Chapter 1 Neuroculture, A New Cultural Revolution. Francisco Moore 1.1 Introduction. What is culture? The definition of this concept has certainly proved as elusive as one for happiness, and little consensus amongst researchers can be found. Moore 2012a. Over half a century ago, Kroger and Kluckholm, 1952, making a brief summary of the more than 160 definitions of culture, concluded that culture consists of patterns, explicit and implicit, of and for behavior acquired and transmitted by symbols, constituting the distinctive achievements of human groups, including their embodiments and artifacts. The essential core of culture consists of traditional, i.e. historically derived and selected, ideas and especially their attached values, culture. Systems may, on the one hand, be considered as products of action, and on the other as conditioning elements, of further action. I would like to highlight the historical feature within this definition, the fact that cultures appear over time, renewing, in these sequences, the readings of values and norms that govern social interactions. From this derives the question, are we, now, on the verge of a new culture? Both humanistic and scientific thinkers suggest as much. For instance, in a public lecture at the Philosophy and Epistemology International Conference celebrating the 30th anniversary of the Piaget Institute in Portugal, 1999, in which he was honored, George Steiner said almost prophetically, all cultures are mortal, all religions too. All are mortal cultural events as mortal are the men who produce them. And it is now that there is a transition period. We are now entering a post-religion era. Christianity will die as Marxism did. What will fill the void? What awaits us? What will be born? As I recall, Steiner did not elaborate very much beyond justifying these questions historically and philosophically, but he certainly emphasized the possible emergence of a new way of thinking in which critical and analytical thinking would play major roles. Edward Wilson stated in his book The Future of Life, 2003, that it was time to change to a culture of life-sustaining permanence of both ourselves and the biosphere. He advocated looking within the mind, gesturing towards the inner workings of the brain to discover its functioning by thoughts, emotions, and feelings out of which the creation and the succession of different cultures have been molded. Science, that is, physics and astronomy, biology, and biological evolution is producing a revolutionary change in our vision of the human world. Many people see in science the 1.2 neuroscience and the human brain these days. Neuroscience is starting to be viewed as a field whose scope extends beyond the understanding of neural mechanisms to trying to achieve comprehension of the psyche and human nature itself, a combination of brain and mind, biological entity, and psyche. Neuroscience and, in particular, cognitive neuroscience, are offering tremendous insight into both these aspects of humankind. We are today facing rapid and continuous expansion in our knowledge about the human brain. It is fairly well established that the brain is a permanently changing organ in both structure and function, continuously absorbing and transforming information from the environment. Jenkins et al. 1990, Moore et al. 2007. This flow of information is not just a passive processing in which an immutable area of the brain or a distributed system in the brain process it using an unalterable code. The brain is a neuronal plastic organ in which neuronal processes are constantly feeding back to alter the processor, the brain, and the person attached. We know today that these plastic changes are generated in neurons and pathways that release neurotransmitters and activate receptors which, in turn, will activate genes, new synthesis of proteins, new receptors, and other membrane components which, finally, result in morphological and physiological changes of neurons and of neuronal circuit activity. Moore 2007. It is in this dynamic way that the chemistry and physics of the brain is transformed into biochemistry, which in turn transforms the anatomy and physiology of the brain, on into behavior, in a continuum in time and space. Considerable neurobiological evidence now exists about the activity of different sensory systems, in particular the visual system, and the perception and consciousness of what is visually perceived. In this respect, vision has contributed to improving the understanding of the brain-mind problem. In addition, a considerable amount of neurobiological research and studies in computational neural connectivity using powerful computers, Proteus, and graph theoretical analysis have given rise to hypotheses surrounding the organization and dynamics of complex neural circuits, networks, in the cerebral cortex which form the neural basis for mental functions. Bullmore and Sporn 2009. Research on large-scale models has also provided new anatomical and functional concepts such as those of the criticality hypothesis. Important new research projects have begun which will increase our understanding of the human brain. Looking back, the first human brain project started in the 1980s and tried to provide a comparison of data obtained through different methodologies at different levels of analysis, hoping to throw some light on complex cognitive processes from the most basic pillars, molecules, cells, and circuits. Shepard et al. 1998. Today, new projects are underway. The Big Brain Project seeks to forge new pathways in neuroanatomy. They have already obtained more than 7,400 cuts of the brain and the images obtained have been scanned. Amunds et al. 2013. The Human Connectome Project aims to build a map of the anatomical and functional connectivity of a healthy human brain. National Institutes of Health, University of Washington at St. Louis, University of Minnesota, Harvard University, and UCLA 2013, and the Blue Brain Project, whose final objective is to study the structure of the neocortex creating a molecular simulation, 2013, are both major works in progress. Hopefully the data obtained from these new research projects will provide an important advance in our understanding about how the brain works and, in parallel with progress in imaging techniques, will advance our knowledge about the brain-mind problems, referring specifically to perceptions, emotions, feelings, abstractions, and ideas, thoughts, learning, and memory, and also consciousness and self-consciousness. Particularly in reference to neuroculture, all this progress will have an important effect on our knowledge of the neural basis for neuroeconomics and sociology, ethical behaviors, politics, art, and religion. 1.3 Biological evolution in the brain and the mind. As Theodosius Dobzhansky pointed out, nothing can be understood in biology unless it is analyzed from the perspective of evolution. Dobzhansky 1973. There is not doubt that evolution is one of the basic elements of that continuum which constitutes man. The human brain is the result first, of several millions of years of evolution, and then a product of natural selection over thousands of generations. Reconstructing how the brain has evolved would be one of the most valuable pieces of work for an integrated advance in neuroscience. Without such a reconstruction of such a history we will hardly understand the meaning and functioning of the human brain and therefore its products. In this case, neuroculture, the relation between the sciences that study the functioning of the brain and culture. Edelman and Mountcastle 1978, Moore 2007. In this context it is worth mentioning that among the different biological species, man has the greatest brain volume in relation to body weight. Garrison 1973, with the highest encephalization coefficient, EQ7, compared to his predecessors, the Australopithecines, EQ2. This brain volume in the EQ has been acquired very rapidly through evolution in the last 4 million years, from the Australopithecines, 500 grams brain beat, to the Homo habilis, 600-700 G, Homo erectus, 900-1000 G, and then Homo sapiens, 1300 grams, and Homo sapiens sapiens, 1400 grams, Holloway 2008, Tobias 1997, 1995. However, the size and weight of the brain of present man does not just constitute a quantitative and global 6 Francisco Moore increase of the number of neurons arranged in the same pre-existing pattern of the brain of a primitive primate, but represents also a reorganization of this brain with selective increases and decreases in specific areas. Holloway 2008. More specifically, the brain during those 4 millions of years of evolution suffered a profound reorganization with reductions of certain areas. Area 17 of Brodmann, expansions. Area 10 of Brodmann 6 times larger than the corresponding area of a chimpanzee or Area 7. Also, asynchronic reorganization of some key brain areas such as the orbitofrontal cortex and asymmetrical hemispheric reorganizations, right versus left brains, occurred during this period of time. Holloway 2008. The macro and micro-internal reorganization, progression and regressions, of specific brain areas, Brodmann areas, occurred during that long period of evolution. Change-out and Chabelain 1995, is particularly relevant when considering the last reorganization, selective and profound, of the prefrontal and orbitofrontal cortex with its key significance for understanding human behavior. Holloway 2008. The prefrontal cortex, together with the parietal and temporal areas, those parts of the brain generically called association areas, seems to have developed in parallel to the acquisition of mental capacities. During evolution, those areas of the cerebral cortex have selectively increased their volume and the number of neurons of which they comprise, as well as enduring a large reorganization when compared to their predecessors. As an estimation, it has been suggested that the chimpanzees have accumulated 3.4 billion neurons compared to the 8.5 billion cumulative neurons in the brain of the Homo sapiens sapiens. Garrison 1976. Evolution has followed multiple and unknown routes to form the present species, including man. Garrison 1973. It is possible that many neural circuits in the brain have changed their function throughout evolution. Functions of parts of the brain that first appeared with a specific survival value and specifically determined by certain environmental conditions at some time could well have changed their functions at other times, readapting them to new conditions of the environment. Gisolfi and Moore 2000. However, it should be pointed out that our current knowledge about the evolution of the human brain is very fragmentary. Many pieces of the puzzle remain missing. The newly discovered Homo georgicus points to a probably reevaluation of the paleoanthropological map, Lord Keepanage et al. 2013. Uncovering how the different parts of the brain were developed, shaped, and reorganized in relation to specific environmental determinants could help to further understand the codes orchestrating the higher functions of the human brain. Gisolfi and Moore 2000. 1.4 Neuroculture. The very rapid progress in our understanding about how the brain works is giving rise to a new way of thinking, changing knowledge about established concepts in philosophy, ethics, law, sociology, economics, art, and religion. New ways of thinking have already begun, with the neurodiscourses and practices found in neurophilosophy, neuroethics, neuroculture, a new cultural revolution. 7 Neuroeducation, neuroeconomics, neuroaesthetics, and neurotheology. This is Neuroculture, Moore 2007, Rolls 2012, a culture based on the sciences of the brain which brings with it a reassessment of the humanities, a bridge by which those two large bodies of knowledge, science and humanities, will join. Neuroculture offers a slow process leading to the reevaluation of our conception of man. Kendall and Mack, 2003, wrote, W. Heil sciences and humanities will continue to have their own separate concerns. We should, in the decades ahead of us, realize more and more that both are generated through a common computer design, the human brain. The epicenter of neuroculture rests not solely on neuroscience or cognitive neuroscience as such, but on the recognition, once again, that human existence is the product of a long process of chance and necessities, Monod 1971, that has lasted millions of years. Revealing the neural mechanisms through which man reached his current neuroanatomical organization and its corresponding functional organization will provide a better understanding not just of man in society but also of the world around him. This new perception will relocate man in a renewed position in that same world. Jose Ortega y Gasset, 1983, once said, El pensamiento humano no descubre el universo sino que lo construye. Human thought does not discover the universe but creates the universe. Julian Huxley, 1964, stated that science does not discover things previously existing but creates something new. The workings of the brain are orchestrated through ancestral codes anchored and hidden in its depth, generation after generation. It is out of these that it constructs something new. Neuroculture will give scientific support to those words of Steiner, 1999, who stated that all cultures are mortal, adding the idea that now all cultures and cultural diversities are the result of the functioning of the brain. It may well be too ambitious a prediction, but I seek to propose that this new culture, which we are naming neuroculture, will eventually lead to that unified theory of knowledge proposed by Wilson 15 years ago. Wilson 1998. Neuroculture may in this way produce an impact on human thinking similar to that produced by Darwinism over L00 years ago. It is possible that, for many, neuroculture will represent a backward step, a way of losing the spiritual essence of what it has been so far conceived as the true essence of human nature. However, for many others neuroculture will be an advance, reaching towards the truth about human beings that has previously been hidden, a conception of man, and the greatness of man, based this time on scientific evidence and critical and analytical thinking which provides a reevaluation of those grand conceptions of human nature: education, privacy, dignity, equality, politics, love, friendship, good and evil, truth, freedom, justice, dignity, and nobility. Neuroculture presupposes that nothing occurs and nothing exists in the human world that has not been filtered, back and forth, culture to brain back to culture, through that seed we call the brain. These may be world events, a beautiful work of art, the successful development of a complex mathematical formula, or the deep feeling of having experienced the existence of God. All this frames the concept of neuroculture. Wexler 2006, Moore 2007, Vidal 2009, Frazito and Anker 2009, Rolls 2012. 8 Francisco Moore 1.5 Neurophilosophy, Consciousness, and the Mind-Brain Problem. Neuroculture offers a reevaluation of humanities. At its core it is perhaps neurophilosophy, as stated clearly by Patricia S. Chichlin, arising from the recognition that brain science and the technologies used in its investigations is advanced enough now to have achieved a real breakthrough in our understanding of the brain-mind problem, memory, learning, consciousness, free will. This predicts that if philosophy of mind is developed without an understanding of neurons in the brain, is highly possible to become sterile. Chichlin 1990, 2008. Certainly one of the central themes in neurophilosophy is that of the so-called brain-mind problem, Linus and Chichlin 1996, Linus 2001. For at least 2,000 years, and certainly since Plato, we have had a clear separation of two worlds, that of the brain or matter, occupying space and time, and that of the mind or spirit, occupying time, and only individually experienced and therefore unique. Beakley and Ludlow 1992, Moore 1995. This perspective has been changed with the advent of neuroscience. Only a few decades of research have been necessary to start attempting to bridge those two worlds. Man is product of Darwinian evolution and the mind is a series of processes carried out by the brain. In fact, mind does not exist in the sense of being a real entity or global concept capturing a static or permanent entity. What really exist are mind processes, that is to say, events characterized in terms of the time-varying activity of interconnected and distributed neural circuits in the brain. Time, not space, is the crucial dimension of the mind. Moore 2008. Therefore, for most neuroscientists, mind is not a spiritual, non-material entity, nor a product emerging or caused by the brain and different from the brain. Mind is the activity of the brain itself. The difficulty then arises when considering how feelings, thoughts, and even consciousness, intimate and subjective events non-material which are difficult to grasp using scientific tools, are in fact the activity of molecules and neurons and circuits of the brain. Apart from some important considerations, when talking about consciousness, most neuroscientists believe that there is a link between brain processes and mind processes, and language contributes in a meaningful way to make the two worlds of brain and mind appear to be different. Moore 2008. An example might suffice as explanation. For instance, when we suffer a burn on a finger and describe in neurobiological terms all the events occurring in the spinal cord and brain, that is, sensory receptors, synapses, neurotransmitters, gene activity, electrical potentials, and activation of neuronal circuits in distributed systems and networks of the limbic system, thalamus, and cerebral cortex, cognition, we are already describing the emotional reaction and the cognitive component of pain but in a different language to that of psychology. In other words, the neurobiological events are not producing something different expressed at psychological or mental level, called pain. All the events taking place in the brain are pain, that is, events that are first described in neurobiological terms at one level and then a person feeling it, consciously perceiving it, and verbally expressing it, described in cognitive or psychological common terms. Moore 2000. As stated more radically by Kendall in his Nobel lecture, given in 2000, The New Neuroculture, A New Cultural Revolution. 9 Biology suggests that not only the body but the mind and the specific proteins that participate in those mental processes self-consciousness, and the consciousness of others, the past and the future evolved from our predecessors to hominids. This new biology postulates that consciousness and mental processes are biological processes that, on due time, will be explained in terms of signaling molecular pathways used by nerve circuits that interact among them. This is similar to Patricia Chichlin's humanistic and poetic description. Bit by experimental bit, neuroscience is morphing our conception of what we are. The weight of evidence now implies that it is the brain, rather than some non-physical stuff, that feels, thinks and decides. That means there is no soul to fall in love. We do still fall in love, certainly, and passion is as real as it ever was. The The difference is that now we understand those important feelings to be events happening in the physical brain. It means that there is no soul to spend its post-mortem eternity blissful in heaven or miserable in hell. Stranger yet, it means that the introspective inside one's own subjectivity is itself a brain-dependent way of making sense of neural events. In addition, it means that the brain's knowledge that this is so is likewise brain-based business. Chichlin 2002. At the central core of any neurobiological approach to the processes of mind lies consciousness and consequently, neuroculture. I thought, therefore, that a brief reflection on the neurobiology of consciousness would be relevant here. Consciousness has been addressed from different philosophical or cognitive points of view, Linus and Chichlin 1996. Although these approaches are important, many neuroscientists feel that they will never be sufficient to fully explain what consciousness is unless other studies or theories appear to anchor them at a neurobiological level. For some, consciousness is no longer a philosophical problem but is instead a scientific problem. Ziki 1993, Crick 1994, Edelman 2006. In recent years reports have appeared trying to tackle this problem from the perspective of the brain, Moore 2000, 2009. The problem of consciousness and its definition presents a considerable challenge. There are important difficulties in reaching a formal definition. Crick and Cook, 1990, admitted this in an initial approach to defining consciousness, and they recognized that the most useful way to advance is to use the descriptions of psychologists and cognitive scientists. With such an approach, together with other observations, they reached the conclusion that consciousness is crucially dependent on some form of short-term memory and also some form of serial attentional mechanisms. Tonanai and Edelman, 1998, on the other hand, consider that conscious experience is a process that is unified and private, that is extremely differentiated and that evolves on a timescale of hundreds of milliseconds. See Searle, 1998, and how he addresses the problem of the definition of consciousness. Consciousness or awareness of the external world, sensory perception, has received a great deal of attention from the neurobiological point of view, Linus and Chichlin 1996, Moore 2000, 2009. Of relevance here is the so-called binding problem, which refers to that neural activity required to bind together all properties of an object, form, orientation, color, movement, depth, and so forth, and this has been postulated to be produced by the synchronous activity, neuron firing, of all those neurons relevant to the analysis of these properties of the object. This synchronous neural activity has been suggested to 10 Francisco Mora occur in bursts at frequencies in the 40-60 Hz range, Linus 2001. In addition, the role of attention and reentrant links to the areas activated has been proposed as two fundamental ingredients for consciousness to take place, Tonanai and Edelman 1998. Thus attention seems to play a crucial role in binding, although the exact location and mechanisms of attention are open questions despite the parietal lobe mechanisms that have been considered relevant in this context. Crick 1996. To complicate matters, we know now that attention is not just a simple neural mechanism involving just one single set of neural circuits but is instead several differentiated neural processes according to the different types of attention that have been so far described, Raz and Burl 2006. There have been many other different approaches to consciousness from cognitive neuroscience and neuropsychology, including studies of patients with blind sight syndrome, memory deficits, split brain, unilateral and contralateral neglect, or patients with specific brain lesions, Damasio 1994, Damasio and Damasio 1990. The new techniques for cognitive experimentation such as positron emission tomography, PET, magnetic resonance imaging, MRI, and the most recent recording technique magnetoelectroencephalography, MEG, with a resolution capable of correlating electrical activity of specific brain areas and cognitive events measured in real time, have all contributed considerably to this development, Linus 2001. A brief neurobiological formulation of the most relevant theories of cognition and consciousness, those of Crick and Cook, 1990, Tonanai and Edelman, 1998, 2004, and Linus and Chichlin, 1996, 2004, will be of use here. Crick and Cook, 1990, proposed that despite the many different forms of consciousness could take at any moment, this could be related to one or a few basic neurobiological mechanisms having at their core a particular type of activity and a transient set of neurons that use a subset of a much larger set of potential candidates. This speculation led Crick and Cook, 1990, to ask which and where these neurons are, and how they are special, connections, pattern of firing, etc. Tonanai and Edelman, 1998, criticized this approach after considering that conferring this property on neurons seems to contribute to a category error, in the sense of ascribing to things properties they cannot have. In the light of classical lesion and stimulation studies and neurophysiologic studies, they propose what they call the dynamic core hypothesis of consciousness. We propose that a large cluster of neural groups that together constitute, on a timescale of hundreds of milliseconds, a unified neural process of high complexity be termed the dynamic core, in order to emphasize both its integration and its constantly changing activity patterns. The dynamic core is a functional cluster. Its participating neural groups are much more strongly interactive among themselves than with the rest of the brain. The dynamic core must also have high complexity. Its global activity patterns must be selected within less than a second out of a very large repertoire. Perhaps one of the original formulations of this hypothesis is that the dynamic core is conceived not as an invariant set of neurons or circuits distributed throughout the brain, but as a set of circuits that may change over time and also that at times could underlie conscious experience while other may be involved in unconscious processes. An important component of the neuroanatomical substrates of this dynamic core could include the thalamocortical connections, both posterior and anterior regions. Tonanai and Edelman 1998. Neuroculture, a new cultural revolution. 11 Finally, Linus and Pear, 1996, Linus 2001, have proposed that, in fact, the thalamocortical system, which comprises a collection of specific thalamic regions, the ventrobasal complex and the nonspecific, middle line nuclei, and a set of cortical counterparts that create resonant functional states, is a central component of the cognitive substrates of the brain. They maintain that the 40 Hz oscillations that can be recorded in many areas of the cerebral cortex are the resonance of neuronal oscillations in specific thalamic nuclei. These oscillations, which exhibit a 12-13 millisecond phase shift from the frontal to the posterior part of the brain, could serve to produce a temporal binding of sensory stimuli. During that unit of time, 12-13 millisecond, the brain would process a single or quantum cognitive event. Cognition, therefore, would be a collection of periods of time. They concluded that integration of sensory events into a larger computational state that underlies cognition is a function of its temporal relation to ongoing oscillatory activities of the brain, Linus 2004. Highlighting those neurobiological hypotheses is important because they were hypotheses, that is to say, they comprise philosophical thinking and, consequently, they constitute extraordinary examples of the integration between science and humanities which is the essence of neurophilosophy and therefore is neuroculture itself, Chichlin 1990. In fact, when talking about consciousness, philosophy may still be permitted to have the last word. As Thomas Nagel, 1991, wrote, science cannot address consciousness unless modifying radically its methodology to identify and analyze the elements of subjective experience. 1.6 Knowledge, pleasure, beauty, and neuroculture painting, music, literature, sculpture, all embellish human life. All cultures have studied, described, or discussed these subjects albeit from a humanistic, subjective, and descriptive perspective. Neuroscience permits a new perspective which we call neuroaesthetics. In its essence, neuroaesthetics is that discipline which is starting to provide some neuronal insights into our understanding of art and beauty. Selakonda et al. 2011, Ishizu and Ziki 2011. Thus defined, neuroaesthetics is, along with the brain-mind problem, at the heart of neuroculture. What is art? What is beauty? Art is a uniquely human activity associated with emotion as well as abstract and symbolic cognition. Art is in fact knowledge and pleasure, pleasure never consummated, never satisfied. That kind of special pleasure which is noted by Immanuel Kant is of the finest nature because it tolerates enjoyment without satiety or exhaustion. Kant 1960, Moore 2006. Neuroaesthetics provides a way, using neurobiological tools, neuronal recordings and imaging techniques such as magnetic resonance or magnetoencephalography, to investigate and dissect the bases in the brain areas, nodes, and distributed neuronal systems, of both knowledge and pleasure. Today we have hypotheses based on scientific evidence, neuronal single recordings, about how the brain may construct the abstractions which are the building blocks of knowledge. Moore 2009. Thus neurophysiologic studies performed in monkeys have provided evidence for neurons in the visual areas responding to a single perspective of an object. 12 Francisco Mora, form, orientation, and depth, but not responding to other perspectives. We also know that there are neurons that respond to the presentation of the entire object irrespective of the perspective presented, giving probable indication of these latter neurons synthesizing all views from the previous neurons. Some of these neurons respond not just to the specific object presented but to different objects of similar shapes and colors. It has been suggested that these last neurons are probably arranged in circuits able to construct an abstraction or ideal object that may accommodate many different objects within that same category. There is speculation that these last neuronal circuits are the basis for the process of abstraction. CP 1999, 2001, Moore 2009. Thus, when nature shows us hundreds of birds of all shapes and sizes, movements and colors, songs and different behaviors, the brain is capable of creating the concept, the idea, of a bird that would summarize all birds in the world. This universal bird is an abstraction created by the brain, an idealization of a bird that neither exists nor could exist in reality, thus making the pure and immutable essence of the bird as Plato might have posited. That is how the human brain works, by categorizing and classifying the sensory world of concepts and ideas. Using this brain-based process of abstraction, man attained the basic principles for thought, language, and communication. Art, in fact, is abstract and symbolic cognition, emotion, and communication beyond common emotional or symbolic language. Moore 2006. Perhaps these networks for abstraction are the result of codes acquired through evolution, as has been suggested for language. Chomsky 1965. According to Chomsky, our environment is highly variable and indeterminate and thus cannot be used to offer a complete explanation of the remarkable ability all young children have to learn complex concepts. From this follows that children may already be born with an innate grammar. The same could be applied for the process of abstraction since it shares with language the neural principles of being common to all human beings and being acquired very rapidly in children. In any case, the contents of these networks permit their holders to perform logical operations whose products are thought, language, art, and mathematics, and also possibly to possess the capacity to create ethical values. Agneta et al. 2007. Indeed, it has been speculated that all these operations may be a function of cerebral dominance, based on the existence of associated neural networks distributed among different areas of the cerebral cortex, thalamus, and brainstem, including the prefrontal cortex, dorsolateral prefrontal cortex, medial and lateral sectors of the orbitofrontal cortex, the anterior cingulate cortex, and regions of the superior temporal cortex. Selakonda et al. 2004, Agneta et al. 2007, Ishizu and Ziki 2011. Beauty, Kawabata and Ziki 2003, Ishizu and Ziki 2011, requires, along with the process of abstraction, something of an emotional plus. Today we know in part how the flow of sensory information, from sensory receptors to thalamus and cerebral cortex, reaches the limbic system, emotional frame, amygdala, and orbitofrontal cortex, where it is labeled with reward or punishment, pleasure or pain, roles in Grabenhorst 2008, Pesso 2008. It is after this emotional labeling of sensory information has been performed that cognitive processes are elaborated in the association areas of the cerebral cortex, Pesso 2008. Therefore the brain, and particularly the brain of an artist, already works with ideas in neuroculture, a new cultural revolution. 13 abstractions that are emotionally colored, Moore 2009. This should be very relevant to understand the act of creation and the capacity of a work of art to evoke beauty. But what seems more interesting when talking about beauty, and especially in relation to individuals contemplating a work of art, whether this painting, architecture, or sculpture, is the hypothesis suggesting that beauty is not something inherent to the artistic work itself but is in fact created by the observer. In other words, the beholder would actively create in his own brain his own conception of beauty which would involve both, in abstract and in the particular, emotion and pleasure. Furthermore, it appears that when the creative personal process of beauty is produced in many people in front of a specific masterpiece, it is then that the work is recognized as universally sublime. Ziki 2001, Moore 2007. Creativity, like ethics, beauty, decision-making, or the ability to think or reason, is not located anywhere in the brain. To create means having the ability to get excited and think, learn, remember, imagine, and all these are brain functions whose processing is distributed in areas, neural systems, and specific networks functioning within codes of time, not space. Bowden and Gentleman 2003, Tanios et al. 2008, Moore 2009. Creativity is an important ingredient in any artistic activity. It is the capacity to do new things, therefore, that enables the artist to capture on canvas, wood, rock, or holograms feelings, abstracts, and ideals. It has been speculated that the artistic creativity may emerge from that clash between the abstractions created by the brain, with its emotional component, unique and personal, and the concrete sensory objects of the world from which precisely those same abstractions have been constructed. Zika 2001, Moore 2009. Think of this as something like an unconscious dissatisfaction caused by a mismatch between mental objects and real sensory objects, between ideas of the objects created by the brain and the real objects themselves. Something like a divorce between the tree the artist sees, which is real, and the tree that the artist constructs unconsciously on the screen of his mind. From that conflict, an emotional reaction arises, leading to that dissatisfaction, frustration. It could be precisely this frustration that acts as the starter of the creative process. The creative act would then stand as the need of the artist to find a personal satisfaction through his work of art, with this work no longer reflecting an objective reality but his mental reality. Ziki 2001, 2004a, 2004b, Moore 2009. In summary, neuroaesthetics offers an explanation about how the appreciation of art and beauty is linked to the activity of multiple brain regions, pathways, and networks, and how this activity is tied to the evolution of Homo sapiens, and the development of language and hierarchical social grouping, and further modified by cultural exposure. Seidel 2010, Selakonda et al. 2011. Neuroaesthetics also helps develop neuroscience and neuroculture through the study of paintings and artists since these provide hints on the impact on culture and the function of the brain. Conway 2012. 1.7 Neuroculture and the Unity of Knowledge. Neuroculture, as I stated above, would be a new cultural event trying to bring together all knowledge into a single conception of man, a unified theory of knowledge. 14 Francisco Mora, Wilson 1998. Over the past few thousand years, man has analyzed every aspect of the universe, included himself, dividing this universe into pieces as it is done now. Every group of scientists in every discipline, using the available tools, has analyzed their field of study by dividing and subdividing it, and then, at their level of analysis, tried to understand and describe the meaning of that little piece of reality. We are now starting to become aware that because everything is a continuum in the universe, an acceptable understanding of a single piece of reality can never be achieved since its full meaning only exists when linked to another fragment of that same reality, sometimes to a different level of organization. Moore 2007. At each level of study, science in general, and neuroscience in particular, has created its own tools of analysis which include language of description and understanding specific to it alone. The science of man is like a Tower of Babel with many people in it, speaking many different languages and, therefore, not understanding each other. The time has come for neuroscience and cognitive neuroscience to try to combine and build bridges between levels of analysis, to approximate languages in order to provide a better understanding of the unique reality which is man. That is, as I see it, one of the major tasks of neuroculture. Moore 2007. One of the key events in such an approach is to understand that from one level of analysis to the next, there is a jump which implies the emergence of new properties in the new level which are not reducible to those of the preceding level. These new emergent properties, however, are tightly bound and completely dependent upon the elements of the preceding level. The most simple and classical example of this is water. Water is made up of oxygen and hydrogen atoms. However, we know that oxygen by itself and hydrogen by itself are not water. That particular molecule, called water, with all its peculiar components, oxygen and hydrogen, are acquired when a particular link between the atoms of oxygen and hydrogen is formed. We know that the laws governing the molecule of water are different from those governing the atoms of oxygen and hydrogen. We also know that the properties of water are not reducible to those of hydrogen and oxygen when separated. But when oxygen and hydrogen are linked together, an emergent new thing, the molecule of water, appears, and with it new laws governing it. Moore 2000. In neuroscience, considerable effort is devoted to stitching together the different levels genes, molecules, organelles, microcircuits, neuronal compartments, nerve cells, specific regions, nodes of distribution and distributed systems up to performance, mental operations, and cognitive systems, Chitland and Sejanos in 1992, which may in time shed light on those complete and complex cognitive processes, mind and consciousness. Thus, it may provide a solid basis for the emerging science of human nature, Fowler and Scriber 2008, Edelman 2006, and with this the consolidation of neuroculture. 1.8 Conclusion. Neuroculture may offer a new vision of humanity and society based on knowledge about how the brain works with help from the perspective of evolution. It might give rise to a neuroculture, a new cultural revolution. 15. New way of thinking, changing our understanding of established concepts in philosophy, ethics, law, sociology, economics, art, and religion. Neuroculture may eventually produce a reassessment of the humanities and may provide a bridge by which science and humanities can join, thus creating a unified theory of man and society. Chapter 2. Art, meaning, and aesthetics. The case for a cognitive neuroscience of art. William P. Seeley. It is important to note that I am not suggesting that we should directly import the results of empirical psychology to aesthetics. The direct application of empirical results in aesthetics can, and very often does, go terribly wrong. What I suggest is that aesthetics should take some new paradigms of philosophy of perception seriously. The specific paradigm I am interested in here, the paradigm of multimodality, is based on a large body of empirical research. However, my aim is not to urge an empirical turn in aesthetics, but to urge a turn in aesthetics towards philosophy of perception, and this sometimes entails a turn towards empirically informed philosophy of perception. 2.1 Introduction. The philosophy and psychology of art often behave as estranged bedfellows, fighting tooth and nail over absent common ground that neither concedes could exist. Empirical aesthetics is predicated on the claim that philosophical studies of art are methodologically suspect. The latter field has been defined as a speculative aesthetics grounded in deductive inferences drawn from the subjective judgments of experts. On this account, philosophy of art, at best, reflects the subjective tastes of critics and theorists. Early 1971, Fechner 1876, Martindale 1990. Philosophers behave no better. They claim that it is a category mistake, an error in logic, to ground a theory of art in behavioral studies. Questions about the nature of art are questions about the structure and validity of artistic conventions, questions that can be no more answered by studying the preferences and physiological responses of large groups of naive subjects than analogous questions about the validity of moral beliefs. Dickey 1962, Wittgenstein 1966, but see also Carroll et al. 2012, Carroll and Seeley 2013b. My suggestion, borrowing the letter, but perhaps not the intent, of 20 William P. Seeley Benson comment above, is that there is something to be learned in a methodological rapprochement on both sides of this great divide. Philosophical questions about the nature of artistic salience and the role evaluative judgments play in our interaction with artworks can be modeled as questions about the influence of cognitive and affective processing and perception. Philosophers would do well to pay attention to psychological theories that address the ways these variables influence our engagement with artworks. Likewise, psychology of art attributes a role to aesthetic appraisal in our engagement with artworks that is not consistent with contemporary artistic practices. Empirical aesthetics would, therefore, do well to pay attention to the range of ways philosophers of art model cognitive, affective, and aesthetic influences on judgments of artistic salience. In what follows, I propose a model for a cognitive neuroscience of art that bridges the gap between philosophy of art and empirical aesthetics and discuss how the model resolves two standard philosophical objections to empirical aesthetics. 2.2 Art, aesthetics, and psychology. The history of mistrust between philosophy of art and empirical aesthetics can be traced to a disagreement about the nature of artistic salience. Think of it this way. Why would the subjective judgments and intuitions of art critics be of any interest at all to philosophers of art? This seems like odd evidence on which to build an objective, general theory of art. Well, ontological questions about art are to a large extent questions about the conventions governing art, categorical and evaluative, but more on that later. Judgments about a range of artifacts. If we want to know about these conventions, who should we ask, or better, whose behavior should we be interested in, experts or non-experts? It seems like the place to start is with people who understand the language, so to speak. Wittgenstein 1958, Dickey 1962. The ability to evaluate the judgments of non-experts in these contexts depends on a prior understanding of the structure of these conventions that are embedded in the behaviors of art experts. I suppose the worry expressed by empirical aesthetics is that this might render artistic judgments subjectively arbitrary and elitist. However, this does not necessarily follow. The claim is not that the judgments of experts arbitrarily determine the artistic conventions of a community. It is rather that expert judgments codify the shared practices that define an artistic community and in so doing reflect the conventions against which artistic judgments and behaviors are evaluated within that community. Research in empirical aesthetics replaces the explicit judgments of expert consumers with physiological measures of arousal constitutive of, at least, the feeling, and in some theoretical contexts the content as well, of aesthetic experience. These physiological measures are treated as objective measures of aesthetic interest and appraisal that generalize across art experts and ordinary consumers and so putatively count as markers of the artistic salience of the formal, expressive, and semantic features of artworks within a community. The thought is that artworks are a natural kind of sorts defined by a common capacity to trigger aesthetic responses in consumers, however that might work. This kind of view art, meaning, in Aesthetics 21 is what philosophers call an aesthetic theory of art. Aesthetic theories of art collapse the concept of artistic salience into the concept of aesthetic salience, or reduce the former to the latter, if you prefer. Empirical aesthetics associates the aesthetic salience of artworks with a capacity to produce a robust, objectively measurable, unified class of physiological responses in consumers. This, in turn, putatively warrants replacing the judgments and intuitions of experts about the nature of art with objective measures of the physiological responses of groups of ordinary art consumers. Perhaps no one really holds the kind of strong non-cognitive aesthetic thesis expressed here. Nonetheless, the objective measures of arousal used to evaluate judgments of artistic salience in empirical aesthetics are aesthetic measures. See Billy 1974, Chatterjee 2012, Sylvia 2012. So, on the surface of things, it looks as if empirical aesthetics relies on an aesthetic theory of art. The trouble is that a broad range of contemporary artworks are explicitly non-aesthetic, and, in the case of aesthetic works of art, there is no guarantee that the aesthetic responses of average members of an artistic community will track the correct use of the conventions governing artistic judgments and behaviors within that community. 2.2.1 Aesthetics and the philosophy of art. The terms aesthetics and philosophy of art are each used in ordinary contexts to refer generically to philosophical studies of art. However, these terms are not synonymous and the equivocation in this casual, non-reflective use of language is significant. The category of aesthetics is broader than the category of art. It includes snowy mountain vistas, stormy coastal landscapes, cozy capes and cottages with tidy lawns, industrial machinery, automotive design, and even the coffee pot on your kitchen counter. It also includes a range of artworks. The category art is broader than the extent of this latter, limited range of aesthetic artifacts. It includes formalist aesthetic abstract expressionist paintings and aesthetically striking Flemish landscapes from the 17th century. But it also includes a full range of non-aesthetic conceptual works like Robert Morris ephemeral installations, e.g. Threadwaste, 19,681, and Steam, 1968/92, Robert Rauschenberg's Combines, e.g. Monogram, 1955-59, 3 Jasper Johns paintings of numbers and letters, e.g. 0 through 9, 1961, 4 John Baldessari's paintings composed of text and definitions, e.g. Tips for artists who want to sell, 1966-68, 5, and Sol Lewitt's location drawings, e.g. Wall Drawing 305, 1977.6 The concepts art in. Aesthetics therefore track different dimensions of the range of artifacts that we categorize as artworks, and philosophy of art represents a broader, more inclusive definition of art. This is critical. It is certainly the case that some artworks are constructed for the purpose of displaying their aesthetic properties. However, many more, and most likely the majority, of contemporary artworks are not like this. They are rather conceptual works. They express a concept or idea, challenge our conception of art, or perhaps reveal something to us about underlying biases within our communities, e.g. the works of John Baldessari, Joseph Kosuth, Robert Berry, Robert Morris, Wesley Lewis, the Judson Dance Theater Workshop, Barbara Kruger, Jenny Holzer, or Adrian Piper. The trouble is that these works are not intentionally designed to trigger aesthetic experiences in consumers. In fact, many of them are expressly anti-aesthetic, designed 22 William P. Seeley to draw attention to themselves as the ordinary, non-aesthetic objects, events, or actions that they are. Aesthetic theories of art would exclude these works from the category art. Therefore, if empirical aesthetics depends upon a tacit aesthetic theory of art, it represents a narrow view of art that is inconsistent with contemporary practice. A similar difficulty arises for the classification of aesthetic artworks themselves. Recall that the range of aesthetic objects, scenes, and etc. is broader than the range of artifacts we classify as artworks. What then distinguishes artistic from non-artistic aesthetic objects? Consider Danto's discussion of Warhol's Brillo boxes as a limiting case. See Danto 2000. The original Brillo box is an aesthetically rich marketing device designed by a second-generation abstract expressionist painter named Steve Harvey. Harvey created the canonical Brillo box while moonlighting in commercial design to make a living. We can perceptually discriminate Warhol's facsimiles from the original by their relative size. Warhol's are larger, and material. Warhol's are made of plywood. But these visible differences don't alone suffice to disentangle which is the artwork. We could, to lapse into philosophical fantasy, imagine a Martian, or even a pigeon with similar perceptual capacities to humans. See Danto 2003. Mistaking Harvey for a Warhol for that matter, I suppose that we could imagine a naive consumer with an adequate understanding of pop art but limited knowledge of Warhol's works within this category making the same mistake. Further, given that Warhol's Brillo boxes reproduce the original visual design fairly accurately, they share the same range of, or at least exhibit similar, dynamic, colorful aesthetic properties as Harvey's. The two types of artifacts aren't just visibly indiscernible in this regard, they are arguably also aesthetically indiscernible. What differentiates them as exemplars of different categories of artifacts, one an artwork and the other a commercial design object, is therefore neither their visible nor their aesthetic properties. Danto argued that what enables us to disambiguate these two sets of artifacts to different categories is the semantic salience of their visual design, or how these formal aesthetic properties were used to convey the content of the works in either case. Harvey's was a red, white, and blue visual celebration of the joy of Brillo intentionally designed to entice us to purchase a cleaning product. Warhol's was a pop art conceptual challenge to the dominant, formalist, abstract expressionist aesthetic of the time. Or, the artistic salience of the formal aesthetic properties of Warhol's Brillo boxes lies in what their hard-edged formal design revealed about the then dominant conventions governing artistic practices within the New York avant-garde art community. The aesthetic features of Harvey's Brillo box, in contrast, simply don't have artistic salience. Warhol's work is conceptual, an expressly anti-aesthetic example of pop art. Someone might argue, consequently, that this is a bad test case. However, the model Danto proposes applies equally to works of pure abstraction as well. Consider, for instance, Jackson Pollock's one, number 31, 1950. 7 ordinary consumers are struck by the energy of Pollock's monumental canvases, by their chaotic construction, perhaps exemplified in their failure to resolve perceptually into stable geometric patterns. But the standard interpretation of these works locates their artistic salience in the trace of the artist's gesture visible in Pollock's brushstroke, in the expressive activity of the artist and the way this aspect of the painting self-consciously reflects both Clement Greenberg's reductive formalist art, meaning, and Aesthetics 23 Aesthetics, Greenberg 1960, and Harold Rosenberg's concept of action painting, Rosenberg 1952. The artistic salience of these works therefore lies in the way they exemplify abstract expressionism as a mid-20th century theoretical position about the nature of art, not their dynamic formal structure per se. The discussion of Brillo boxes in 1, number 31, 1950 reveals something important about the nature of artworks. They are communicative devices. We typically engage artworks as intentional objects with cognitive content, as the product of a range of formal and compositional choices made by the artist, choices that carry information about their content. We are interested in how they were constructed, or perhaps better, in why they were constructed the way they were even when they are canonically aesthetic artworks. It can, as a result, be argued that the artistic salience of the formal compositional features of a work lies in their semantic salience, and how they have been used to express the meaning or content of the work. Of course, artists often use aesthetic devices as part of the array of formal compositional strategies they use to convey the content of their work. However, the artistic salience of these features lies in their semantic salience, in what they contribute to the content or meaning of the work. This is true of the broad range of artifacts that count as artworks, from anti-aesthetic conceptual works to those limited cases where the content of a work simply involves the expression of some set of artistic conventions for constructing aesthetic artworks. For instance, the artistic salience of landscape paintings lies, at least in part, in what the stylistic choices of their painters revealed about the aesthetic conventions of their time, e.g. the way the skewed scale of Hudson River School paintings reveals mid-19th century American beliefs about the relationship between man and nature and the current politics of American expansionism. A standard philosophical objection to aesthetic theories of art can be used to illustrate this point. Aesthetic theories of art define artworks relative to a capacity for producing aesthetic experience. This entails that where an artwork doesn't succeed in triggering an aesthetic experience in consumers, it isn't an artwork. If sound, this would mean that there could be no failed artworks. This, in turn, would mean that generations of folks who have toiled away in studios, struggling in vain with the creative process, were in fact not engaged in art making at all. They were doing something else altogether. Of course, philosophical arguments with absurd conclusions like this one are rarely intended to be taken literally. The point of a philosophical reductio ad absurdum is more often than not to suggest that there is something wrong with some aspect of an argument that deserves attention and modification. Art is a success term. Its ordinary usage carries some degree of normative, or evaluative force. Some artifacts manage to achieve arthood, and we value them to the degree that they do. The question is, what are the criteria that govern our judgments in this regard? Aesthetic theories of art argue that the candidate criteria is the capacity of an artifact to trigger an aesthetic experience. However, this won't do. Failed aesthetic artworks are, nonetheless, artworks, and we judge them to be so despite the fact that they fail to produce aesthetic experiences in consumers. How is it, then, that we come to categorize members of this class of artifacts as artworks? We readily see that they were designed with an intention 24 William P. Seeley to function as aesthetic objects, that they are fit to some set of formal compositional conventions for producing works in some aesthetic category of art, for instance 19th century Hudson River School painting as opposed to mid-20th century minimalist sculpture or late 20th century installation art. What matters in categorizing an artifact as an artwork is the fit between the intended content of the work and the conventions governing categorical judgments about the class of artworks it belongs to. A failed aesthetic work, then, is an artwork regardless of whether it ever succeeds in triggering any actual aesthetic responses in consumers. There is nothing particularly special about art in this regard. Artifacts achieve sawhood, or any sort of toolishness, when they meet the categorical criteria for being a saw, or any sort of tool. Likewise, we value them for their success in achieving this status. What makes something a saw is that it has a blade suited for tearing some material. A saw blade may fail to realize this function. Toothless friction saws designed for precision metal cuts are particularly bad at cutting wood. Similarly, crosscut saws are ill-suited for making rip cuts. But we still categorize them as saws. A length of rope coated in an experimental abrasive designed to cut plastics remains a saw, by virtue of its design as a blade for tearing material, even if the novel abrasive wears away too quickly to be effective. Likewise, a Claes Oldenburg soft saw sculpture is a saw of sorts even though it would fail to realize this function in any context. 2.2.2 Art, Aesthetics, and Appreciation. We might dub the issue discussed in the previous section the problem of artistic salience. The problem of artistic salience points towards a second philosophical challenge to empirically minded theories of art. Some philosophers have argued that questions about artistic appreciation, evaluative question about whether a work fits the conventions governing artistic practice, and if so whether it has been done well or poorly, are the critical questions that ground an understanding of art. This seems like too strong a position. Philosophers have always been interested in more general ontological and epistemological questions about the nature of artworks and our interactions with them. Aristotle, for instance, wrote on the narrative structure of tragedy and the nature of our psychological engagement with characters in the poetics. There are similarly a range of interesting questions about the nature of installation art that are independent of questions about the value we assign particular installations. Urban 2013. What are the identity conditions governing an installation? Is an installation, like a musical score, a repeatable recipe? How should the installation crew implement the relationship between a particular installation and the particular space of the gallery? What if the artist doesn't leave explicit instructions, is vague about them, or simply isn't around to query for advice? Should the work stay as true as possible to relevantly similar prior installations? If so, which ones? If not, what sort of constraints govern the creative judgments of the curator? These aren't evaluative questions. They are questions about the way artworks work, questions about the conventions governing artistic production, understanding, and related psychological processes. Nonetheless, evaluative questions are among the questions of philosophical or psychological theory of art should art, meaning, an aesthetics 25 answer. This is a place where philosophy of art and empirical aesthetics agree. Aesthetic appraisals play a critical role in empirical aesthetics. The objective physiological measures of arousal that ground research in the latter field are, in keeping with an aesthetic theory of art, explicit measures of artistic success, evaluative measures of aesthetic interest and appraisal. Evaluative questions germane to artistic appreciation are normative questions, questions about the fit between an artwork and standard conventions governing artistic practice, or whether it was done well or poorly. The strong philosophical claim in this context is that causal explanations of behavior in terms of the causal psychological processes that link stimuli to behavior are irrelevant to normative questions. They apply equally whether or not that behavior is an appropriate response to the target situation or not, whether the arousal measures indicative of artistic interest and aesthetic responsiveness are appropriate to the work, are the product of contextually appropriate conventions and cognitive processes or not. For instance, we can imagine a consumer having a physiologically appropriate aesthetic response to a Jackson Pollock because it reminds them of the innocent exploratory creativity of children's finger painting, perhaps their own child's finger painting. Explanations of aesthetic appraisals in experimental psychology are causal explanations. Therefore, it is argued, they are not sensitive to the appreciative dimension of artistic behavior. Wittgenstein 1966. Imagine, for instance, a study in which participants are asked to match musical compositions to a range of adjectives that expert music scholars and critics have identified as appropriate to those works. Dickey 1962. Appealing to agreement among subjects here would be like appealing to agreement among young children about the meaning of nonsense words, or appealing to agreement among toddlers about the syntactic well-formedness of sentences. What really matters in these contexts is something about the conventions governing linguistic practices and how apt the stimuli are to those conventions. This information would already be in place at the start of this kind of study, rendering its results ocioso best. Likewise with preference judgments. The preferences of uneducated novices are not the right kind of evidence to use to evaluate a work. The right place to look is the reflective judgments of experts about the fit between the work and the conventions governing those practices, not the average behavioral response of large samples of novice and expert consumers. Appreciative judgments about artworks are grounded in comparisons between those artifacts and the conventions governing artistic practices for a particular category of art. The success of these judgments rests upon an understanding of that category of art, including knowledge of the normative conventions that determine whether an artwork of that type was done well or poorly. Levinson 1992, Rollins 2004. Philosophical questions germane to artistic appreciation are questions about the content of these conventions and why they have normative force, or how they constrain our evaluative judgments. These are not questions that can be answered by averaging the behavioral responses of ordinary untrained participants loosely associated with an artistic community. Consider the analogous case of morality. Ethical questions about moral behavior, questions about how one ought to 26 William P. Seeley behave in order to comport oneself as a genuinely moral person, cannot be answered by observing the ordinary day-to-day behavior of members of a community or by polling their preferences. These kinds of studies may reveal how groups of people do behave in a community, but the question about how one ought to behave is a different question. See Moore 1903. Objective measures of aesthetic interest and appraisal might similarly reveal what kinds of artistic judgments groups of people make. However, these are objective measures of a participant's subjective response to an artwork. They do not differentiate between judgments that reflect an appropriate understanding of particular artworks and those that do not. The argument, therefore, is that it is a methodological error, a category mistake, to use behavioral methods and results to address questions about the structure and function of artistic conventions. 2.2.3 A model for a cognitive neuroscience of art. I have suggested elsewhere that philosophical skepticism about the utility of empirical research to any understanding of art is misplaced. Carroll et al. 2012, Seeley 2010, 2011a, 2011b, Cosbelt and Seeley 2007. Cognitive science, in the broadest sense of the term, refers to any of a range of interdisciplinary approaches to understanding how an organism acquires, represents, manipulates, and uses information in the production of behavior. Research in neuroscience of art and empirical aesthetics falls squarely within cognitive science under this interpretation. Artworks are stimuli intentionally designed to trigger a range of affective, perceptual, and semantic responses in consumers constitutive of their artistically salient, expressive, formal, compositional, aesthetic, and cognitive content. Empirical aesthetics and neuroscience of art are methodological tools that are regularly used to model the way consumers acquire, represent, manipulate, and use information carried in the formal compositional structure of painting, films, dances, musical performances, novels, and poems, to name a few, in the processes underwriting canonical cognitive, expressive, and aesthetic artistic responses to artworks. These data can, in principle, be used to adjudicate between competing philosophical theories about the nature of art and our engagement with artworks, and to answer thorny questions with problems of artistic salience and artistic appreciation raised for empirical aesthetics more generally. A sketch for a general model for a rapprochement between philosophy of art and empirical aesthetics emerges from some of the platitudes surrounding research methods in neuroaesthetics and a fairly standard story about artists' productive practices. The local environment is replete with information about the structure, function, and dynamics of objects and events, only a small fraction of which is germane to our current goals and activities at any given time. Perceptual systems, on the other hand, are limited capacity cognitive systems. Selectivity is therefore a critical component of perception. Perceptual systems must enable an agent to select task-salient perceptual features and discard the vast range of distracting information that clutters his or her perceptual world. Recent research suggests that one means to solve this problem is to develop visual routines and other types of perceptual strategies for directing attention to sets of features diagnostic of the identities, affordances, and locations of task-salient objects in the local environment. Art, meaning, in Aesthetics 27, C. Hale and Ballard 2005, Rollins 2004, SCHYNS 1998. Point 8 Perceptual systems can, in this regard, be interpreted as evolved mechanisms for identifying and selecting task-salient information from a dynamic flux of sensory inputs and discarding distractors in the local surroundings. CP 1999. See also Pesso et al. 2002. Stein et al. 2006. Artists have developed systematic methods for selecting sets of diagnostic features from ordinary perceptual experience, rendering them in a medium, and evaluating their salience as productive strategies, e.g. color studies for paintings or storyboards and dailies for film. The resulting formal compositional devices work as communicative strategies because they are directed at the range of perceptual strategies that cognitive systems employ in ordinary contexts to cope smoothly with a dynamic environment replete with sensory information on the fly. Therefore we can hypothesize that we ought to find a close coupling between artists' productive strategies and the operations of perceptual systems. A significant amount of research in neuroaesthetics has been devoted to uncovering, tracking, and evaluating the range of ways artists' formal productive strategies map to the operations of perceptual systems, e.g. Richard Latto's discussion of the relationship between irradiation and lateral inhibition in the retina, Beatrice Calvamarino and Corinne Jola's explorations of the role played by premotor areas in the action observation network in audience engagement with dance, and Nicole Spears. Research on the role played by motor simulation in narrative understanding in text and film, Calvamarino et al. 2008, Jola et al. 2012, Latto 1995, Spear et al. 2009. However, correlations between the neurophysiological operations of perceptual systems and artists' formal compositional strategies do not alone suffice to explain the artistic salience of the formal, expressive, or semantic features of an artwork. Irradiation works to enhance figure ground segregation and the perception of depth in Monet's paintings because lateral inhibition produces half shadows everywhere in our perceptual environment that play an analogous role in ordinary depth perception and object recognition. Latto 1995. Motor simulation, likewise, works as a mechanism to support the role of kinetic transfer in dance communication and narrative understanding in film because it plays an analogous role in action recognition and the perception of biological motion in ordinary contexts. See Carroll and Seeley 2013a, 2013b. Similarly, motor simulation plays a role in narrative understanding in fiction because, or to the degree that, it plays a critical role in the semantic comprehension of action sentences. Fisher and Swan 2008, Spear et al. 2009. What one needs is a further argument connecting the way artworks work generally as cognitive stimuli to the way consumers recognize and understand the artistic salience of their formal, expressive, and semantic content. The notion of an aesthetic appraisal is often called on to do the heavy lifting here in empirical aesthetics. However, as discussed above, the preponderance of non-art aesthetic objects, events, and experiences raises a question about whether aesthetic measures are appropriate measures of artistic salience. A solution to this problem emerges from the observation that there is no ideal formal compositional strategy for artistic production in a medium. Rather, artists must choose how to render their subject matter from a wide range of alternatives. Categories of art in which productive practices are directed towards shared subject matter are the easiest. 28 William P. Seeley place to see this. For example, realistic landscape painting in Hollywood movies, but any exploration of formal stylistic differences would ultimately do. The stylistic variance in what has passed as realistic depiction in this context demonstrates that any of a range of formal compositional strategies suffice to render these environmental features realistically. See Gombrich 1960, Lopes 1995. We might tell a similar story about the range of variants of common stories in movie and theater production. For example, Pierre Coderlos de Lego's 18th century novel Dangerous Liaisons, Christopher Hampton's theatrical version of the same story, or the three film versions by Stephen Frear, Jim O'Heir, and Milos Forman. What are the constraints governing the development of those formal compositional strategies that define the artistic styles of different schools, eras, and artists along with the surface structure of different artworks? The intended content of the work, the expressive, formal aesthetic, and cognitive effects an artist intends the work to have on consumers. What are the constraints on the artistic content of the work? The conventions governing productive and appreciative practices for a category of art. Therefore, the formal compositional structure of an artwork naturally carries information about the conventions governing artistic practices, information that cognitivist models within the philosophy of art argue determines the artistic salience of the expressive, formal aesthetic, and semantic features of a particular work. This entails that artworks are attentional engines, or cognitive stimuli intentionally designed to direct attention those aspects of their formal compositional structure that carry information about their content, including information about the category of art a work belongs to. Carroll and Seeley 2013a, Levinson 1992. Categorizing an artwork as belonging to a particular school, era, or artistic style provides a recipe for how to approach it. This instructs the consumer as to which sets of artistic conventions are appropriate to his or her cognitive and appreciative engagement with the work, e.g. as a satire or dramatic novel, an impressionist, or a Hudson River School painting, or a modernist or a postmodernist dance. A core set of critical questions loosely defines this research model for philosophy and neuroscience of art. Seeley 2013. What are the range of formal compositional strategies that define productive practices within a category of art? How do these strategies function to carry and communicate diagnostic information about the content of these artworks? What accounts for the artistic salience of the expressive, formal aesthetic, and semantic features constitutive of the content of these works? A solution to the problem of artistic appreciation follows naturally from the answer to the last question. The artistic salience of the expressive, formal aesthetic, and semantic features of an artwork lies in the way they reflect the range of artistic conventions that govern artistic practices for the category of art to which it belongs. Danto's discussion of Warhol's Brillo boxes is a canonical illustration of this position. The artistic salience of Warhol's Brillo boxes lies in the fact that they violate, and so cause us to reflect on, the conventions governing productive practices within, and appreciative judgments about, abstract expressionist artworks. Appreciative judgments about Warhol's work involve judgments about the validity of this project in the context of conventions governing avant-garde art, which are conventions governing the reflective use of artistic practices to evaluate the validity of artistic conventions. Warhol chose to art, meaning, in Aesthetics 29 approach this problem using a visually pleasing design. But, ultimately his strategy was to highlight the identity of the work as what it was, an exemplar of an ordinary household object whose salience was tied to its everyday use, not a metaphysically charged, abstract, high art aesthetic object. Other examples of this strategy are Jasper John's Painted Bronze, 1960, Nine and Painted Bronze, Valentine Ale, 1960, Ten and Steve Paxton's Untitled Dance in which he sat on a bench and ate a sandwich, C. Baines and Carroll 2006. We might argue that the visually striking features of the Brillo design are, in this regard, the least successful aspect of Warhol's work. Alternatively, we might argue that he employed a visually striking design to draw attention to its irrelevance to the salience of the artifact as an artwork. 2.3 Hierarchical models in attentional engines. We need a cognitive neuroscience of art because we need a model for how we use semantic content to disambiguate artworks from similarly structured non-art artifacts. For example, works of commercial design. This is transparently obvious in the case of non-aesthetic conceptual art, but it is also true of abstract aesthetic works at the opposite end of the spectrum. The artistically salient content of a work emerges from the way its formal compositional structure reflects the conventions governing artistic practice within the appropriate category of art. The canonical example used to illustrate this fact within philosophy of art comes from Kendall Walton, 1970. Point 11. Imagine two perceptually similar categories of art, Picasso's Guernica 12 and a hypothetical, imaginary category of bas-reliefs that share its formal compositional structure called Guernicas. The artistically salient dynamic features of Guernica are a product of its fractured, dynamic, black and white cubist composition, which Picasso used to express something about the horror of war for the communities within which they are fought. Guernicas are, in contrast, colorless. Their artistically salient dynamic features emerge from the way figure-ground relations give way to a depiction of the chaos of war in shallow relief, in their three-dimensional structure. Guernica is flat. Therefore, relative to the conventions governing bas-reliefs, it is static rather than dynamic. An analogous criticism can be directed at the Guernicas. They are colorless. Therefore, relative to the conventions governing artistic production in painting, they lack an articulated structure sufficient to support the dynamics of Guernica. We need a cognitive neuroscience of art because we need a theory that is sensitive to the way these kinds of conventions govern artistic practice within a category of art, constrain the contents of artworks, and influence our engagement with them. We need a theory that can explain how artworks work as attentional engines to focus attention on formal compositional cues diagnostic for the appropriate category of art, Guernica and not Guernicas, pop art and not commercial design, or abstract expressionism and not finger painting. Point 13. Biased competition theories of selective attention. Desimone and Duncan 1995, Kastner 2004, SOETAL 2002, suggest a model for how artworks function as attentional engines. Recall the problem of selectivity. How do perceptual systems solve this problem? How does an organism flexibly orient its attention to diagnostic information on the fly in the kinds of novel contexts it confronts in everyday behavior? The simplest solution is 30 William P. Seeley that these systems are fine-tuned to perceptual salience. Some environmental features are simply brighter, more vividly colorful, or move differently than their neighbors. We easily orient our attention to them because they stand out in a crowd. The trouble is that the vast majority of behaviorally salient features in the environment simply are not perceptually salient in this way. Certainly none of the keys on my keyboard, the papers on my desk, or the baking products in my cupboard sing out their relative salience to my current needs like a klaxon. Therefore, perceptual systems require an independent mechanism for assigning salience to diagnostic features, for tagging the salience of objects and their features with relevance to me rather than their relative difference from their surroundings. Bayes' competition model suggests that we employ top-down, frontal-parietal, and cortico-pupil attentional networks to solve this problem in everyday perceptual contexts. These networks bias perception by priming the firing rates of populations of neurons and sensory systems to the expectation of diagnostic features at particular locations. A fast first sweep through the perceptual system is sufficient to match minimal diagnostic features to semantic knowledge of the structure, function, and affordances of object and event types stored in declarative memory. Pessoa and Adolphs 2010. This information, in turn, can be used as a scaffold on which to fix perception to direct attention in Bayes' perceptual processing to task salient features, objects, or object parts at expected locations within the visual field. We can tell a similar story about artworks. Some of the features of an artwork are perceptually salient, and so naturally draw our attention. For instance, Winslow Homer rendered the trigger hand of the Union sniper brighter than any other feature in his wood engraving. For Harper's Weekly, the Army of the Potomac, a sharpshooter on picket duty, 1862.14. The morality of the practice of using sharpshooters during the American Civil War was questionable. These soldiers never faced the enemy they engaged, and so it was thought that the use of sharpshooters dehumanized the practice of war. We can't see anything of the face of the sharpshooter in the print beyond a shadowed eye trained on his target down the barrel of his rifle. Our full attention is drawn to his hand on the trigger, which hides his face. The sharpshooter is, thereby, depicted as a dehumanized mechanism of destruction. Likewise, the raw stroke of yellow oil crayon John Singer Sargent used to depict the fishing rod in Val d'Aosta, A Man Fishing, 1907, 15, and the red flowers of the poppies depicted in Monet's Wild Poppies near Argenteuil, 1873, 16 are perceptually salient features. However, the artistic salience of these works does not lie in either the coarse structured yellowishness of the fishing rod or the bright, rough redness of the poppies. Rather, these features function to draw our attention to more general structural features of the works, the dynamic interplay of light on the surface of the pond beside the fisherman and the sergeant, and the generically greenish-brown field of grass waving in the wind that dominates the lower half of the Monet. In fact, the whole composition of the sergeant painting, the orientation and posture of the prone figures lying beside the pond, the gaze of the fisherman, and the orientation of the fishing rod drives the consumer's attention to the coarse, expressive brushwork constitutive of the dynamic depiction of the water. These structural features are diagnostic cues to the identities of the two works as exemplars of an impressionist style of art, meaning, an aesthetics 31 painting. These cues, in turn, let us know how to engage the work, in this case to pay attention to the way the brush strokes are used to depict the dynamic interplay of light, form, and movement in the visual field. What is the mechanism in all of this? Bayes' competition models of selective attention identify a broad network of frontal-parietal and cortico-pupil circuits that facilitate the cross-modal integration of sensory motor and unimodal sensory information in perception. This network includes projections from prefrontal areas involved in spatial working memory, for example, dorsolateral prefrontal cortex, DLPFC, to the frontal eye fields, FEF, which are associated with endogenous shifts of attention, and projections from both FEF and DLPFC to superior colliculus, SC, fulminor, and the lateral geniculate nucleus, LGN, in the thalamus, Kastner 2004. These subcortical areas are hypothesized to participate in processes critical for neural synchronization, LGN and fulminor, directing eye movements, SC, and the cross-modal integration of visual, auditory, and somatosensory information, SC. LGN is the primary relay station between the retina and the visual cortex. Therefore, attentional priming reaches back to the earliest stages of visual processing, Beck and Kastner 2009, Stein et al. 2004, Pessoa and Adolphs 2010. These feedback projections from prefrontal and parietal areas that are associated with object recognition, spatial working memory, and attention to topologically encoded cortical and subcortical perceptual areas facilitate the integration of sensory information into coherent representations of task-salient aspects of the distal environment, and they account for the influence of categorization processing and perception. Feed-forward projections from perceptual processing areas to these same prefrontal and parietal areas, in turn, function to reinforce perceptual representations and instantiate working memory in a distributed multimodal network. The trick is that our engagement with paintings depends on a capacity to reconstruct their depictive and representational content from diagnostic information encoded in the abstract sets of marks constitutive of their two-dimensional formal compositional structure to recognize objects and scenes in a painting and comprehend what it would have meant for an artist to render them in the particular way they have been painted, e.g. the coarse brush strokes used to depict the pattern of reflected light that gives the water its dynamic appearance in Sargent's Val d'Aosta, A Man Fishing. This requires matching abstract diagnostic cues both to category knowledge and object recognition and knowledge of the stylistic conventions regulating artistic production in a category of art, or recognizing an artwork both as a visual representation of what it depicts and as a member of a category of art. The suggestion is that cortico-pupil attentional circuits, in conjunction with a range of further recurrent connections, including projections from areas T and Teo to visual areas V4 and MT associated with the perception of color, abstract patterns, motion, and depth, play a critical role in this capacity. Hierarchical theories within empirical aesthetics can be used to articulate the range of processes that might influence cognitive and appreciative judgments about the artistic salience of the content of a work. These theories model artistic production and our engagement with artworks as a multi-stage process that includes sensory processes, perceptual analysis, explicit classification judgments, decision procedures, and effective responses. 32 William P. Seeley that underwrite our capacity to recognize the formal compositional and depictive content of a work, understand its semantic representational content, and appraise its artistic salience. Chaturji 2003, 2012, Cosbelt and Seeley 2007, Letter E.T. A.L. 2004, Nadal E.T. A.L. 2008. For instance, Letter and his colleagues differentiate between two distinct kinds of aesthetic responses to artworks, aesthetic judgments and aesthetic emotions. Aesthetic judgments are a product of what they call cognitive mastering, or the explicit classification and subsequent interpretation of the content of a work relative to expert knowledge of stylistic conventions that define artistic schools, movement, eras, and the works of individual artists. For example, Rothko and Motherwell's abstract expressionists' works, or differences between Sargent's portraits and his impressionistic landscapes. Explicit classification is the key in these processes. It specifies the set of artistic conventions that constrain our cognitive engagement with the work. The output of perceptual analyses can then be meshed with salient expert art critical knowledge to yield an interpretation of the meaning of the work in cognitive mastering. A reduction of ambiguity, or uncertainty, see Berlin 1971, by cognitive mastering yields an aesthetic evaluation of the success of a work. Success at the explicit classification, cognitive, and evaluative stages are experienced as changes in affective state that yield a state of pleasure or satisfaction. Letter defines as an aesthetic emotion. Letter argues that content responsiveness will lie on a continuum from naive to expert consumers. See also Seliconda et al. 2002. Naive consumers who lack expert art critical or art historical knowledge will respond to the depictive content of works, evaluating them relative to their success as either representational works or abstract constructions on this model. Point 17 Expert consumers, on the other hand, will exhibit sensitivity to the artistically salient, formal, expressive, and semantic features of the work and the way these are used to generate its art critically salient content. This is precisely what our model would predict. Loosely, explicit classification and cognitive mastering are processes that involve the implementation of judgments about the relative diagnosticity of features of the artwork for its content. These processes in turn, bias processing in frontal-parietal and cortico-pupil attentional circuits, driving our perceptual, affective, and cognitive interaction with the work. See also Chaturji 2003, 2012. 2.4 Artistic salience, artistic appreciation, effective and embodied responses to artworks. We can now return to the questions about artistic salience and appreciation that have driven philosophical skepticism about empirical aesthetics. The first thing to note is that hierarchical theories have resources ready to hand to tackle these issues. These theories model our engagement with artworks as a multi-stage process that employs expert art critical knowledge to integrate perceptual, cognitive, and affective aspects of our engagement with artworks. There are other theories within empirical aesthetics that model our engagement with artworks as a cognitive process. For example, prototype preference, Martindale and Moore 1988, and processing fluency theories, River 2012. The virtue of hierarchical theories over these other approaches is that nested sets of hierarchically related art, meaning, and aesthetics 33 recurrent circuits enable them to model explicitly the way the formal compositional features of a work achieve artistic salience, the way they carry the information about salient artistic conventions constitutive of the formal aesthetic, expressive, and semantic content of a work. Nonetheless, and this is the real rub, all of these theories model the influence of cognitive variables in our engagement with artworks as a part of the process of aesthetic appraisal. They, like aesthetic theories of art more generally, treat artworks as aesthetic engines. For instance, Chaturji, 2003-2012, argues that aesthetically salient, perceptual, expressive, and semantic features of artworks drive top-down processing and attentional circuits in our engagement with artworks. This, as discussed earlier, narrows the potential explanatory scope of these models and opens the door to the problems of artistic salience and appreciation. However, if we drop the aesthetic desiderata and treat artworks as attention engines instead, these problems fall away as spurious worries. The problem of artistic salience is a question of what differentiates artworks from non-art artifacts. This is a philosophically important question. A minimum desiderata for a theory of art is that it explain how we sort the range of artifacts that fall under that category, how we discriminate artworks from non-artworks and sort them into salient categories of art. Theories in neuroaesthetics, and empirical aesthetics more generally, treat artworks as cognitive stimuli like any other and model our engagement with art as a product of everyday cognitive processes. The challenge for any model like this that treats artworks as ordinary cognitive stimuli is to explain then how we manage to sort the artworks from the other everyday perceptual stimuli. One common strategy in neuroaesthetics is to simply dodge this question and study the way a set of standard, successful, formal aesthetic strategies work. For example, discussion of the radiation and decay effects in Monet's paintings, Lado 1995, Livingstone 2002. In these contexts, researchers define artistic salience relative to aesthetic salience, take the aesthetic salience of a well-accepted formal strategy as given in a particular context, and then explain associated aesthetic effects as products of our perceptual engagement with the work. However, as discussed, the artistic salience of the aesthetic features of a work of art is not a perceptual given, but rather depends on the category of art to which we assign the work, to the way we differentiate it from other non-art artifacts and sort it from its other artistic cousins. The diagnostic recognition framework suggested by biased competition theories of selective attention models our engagement with artworks differently. In ordinary perceptual contexts, minimal sets of diagnostic features suffice to enable an organism to recognize the identities and affordances of objects and events perceptually. Koslin and Koenig 1995, SCHYNS 1998. How might this work? A fast first sweep through unimodal perceptual systems might suffice to match sparse sets of coarse-coded sensory stimuli to declarative knowledge of the structure and function of categories of objects or events stored in semantic or episodic memory. This knowledge can, in turn, be used to direct attention and prime the firing rates of populations of neurons across the full range of perceptual modalities to other environmental features diagnostic for the task at hand. These processes enhance the encoding of task-salient perceptual information, inhibit the encoding of potential distractors, and thereby facilitate the smooth and efficient selection in Perception 34 William P. Seeley of behaviorally salient information. Categorical knowledge of the structure and function of object and event types therefore serves as a strong determinative constraint that shapes sensory processing, influencing not only what we see, but how we see it. SOETAL 2002, SCHYNS 1998. Artworks can be sorted into unique categories of objects and events defined by media. Sculpture vs painting, productive practices, dance vs performance, content, e.g. portraits vs landscapes, formalist vs conceptual, and formal compositional stylistic features, e.g. Thomas Cole's Hudson River School paintings, Diego Rivera's social realism, Thomas Hart Benton's regionalism, or Robert Bechdel's hyperrealism. These categories of art, in turn, articulate sets of artistic conventions that constrain our engagement with artworks. The identities of individual artworks may cut across categories of art, or categories of art may not sort into functionally discrete sets, but rather form an interlocking web, an integrated network that defines an art world at a time. For instance, Bill T. Jones borrows elements of performance to articulate the narrative content of his choreographed works, e.g. his work about the life of Abraham Lincoln. Fondly do we hope. Fervently do we pray. 18 and Judy Pfaff borrows from Cubism and the painterly drawing style of Jackson Pollock in her sculptural installations, e.g. NYC, BQE, 1987-19 or Deepwater, 1980. Point 20 Recognizing the productive role these shared categorical conventions play in the content of the work is critical to understanding them. A capacity to categorize the formal compositional content of the work in this way guides attention, facilitates the recovery of diagnostic features, and, by the same attentional processes operative in ordinary perceptual categorization tasks, determines the artistic salience of what we perceive and experience in our engagement with artworks. Therefore, treating artworks as attentional engines and acknowledging the productive role of categorization, processing, and attention and perception transparently resolves the problem of artistic salience for empirical studies of the arts. A solution to the problem of artistic appreciation falls out for free on this view of how we recover the artistic salience of the features and content of an artwork. Recall that aesthetic appraisals and other appreciative judgments about artworks are normative judgments about whether a work was done well or poorly, about whether it is suited to a context. Normative judgments of this sort involve comparisons between the formal, expressive, and semantic content of the work and conventions that govern salient artistic practices. For example, conventions constitutive of artistic practices within the category of art to which a work belongs. Psychological explanations are causal explanations, or explanations of the causal psychological interactions between a work and a consumer. The initial skeptical claim is that causal interactions between a consumer and an artwork are immune to the influences of these conventions. This claim is taken to entail that psychological explanations of our interactions with artworks are not sensitive to the right kinds of variables to stand as explanations of the success or failure of appreciative judgments. They can't alone discriminate between normative judgments that are appropriate and those that are not. This simply isn't true of the model articulated here. From the perspective of a diagnostic recognition framework, our perceptual engagement with artworks is driven by attentional processes that are themselves governed by knowledge of the range of conventions that art, meaning, and aesthetics 35 define different categories of art. These conventions are, as philosophers say, constitutive of the way we experience the work. They are productive constraints that determine what we perceive in the work and how we perceive it. Where the work doesn't match the range of conventions appropriate to a category of art, our perceptual expectations will be unsatisfied, our attentional strategies will misfire and remain unrealized. Our experience of the work will consequently be degenerate. It will fail to meet the cognitive goals that drive it and we will appraise it as ineffective. The model I have proposed here, like hierarchical models generally, has the resources to resolve the problem of artistic appreciation because the salient artistic conventions are built into the perceptual processes that enable a consumer to recover the content of a work. Two caveats are in order here. First, a consumer's expert art critical knowledge can be incomplete, incorrect, or non-existent. In these kinds of cases we would expect that the appraisals they generate for artworks in those categories would not adequately track their artistic salience. But this is not a problem for the model. The fit between a work and categorically relevant artistic conventions is the marker of artistic success on this account, not the physiological responses or preference judgments of consumers. We, therefore, have the resources ready to evaluate inappropriate appraisals. Nonetheless, the skeptic may yet find this approach wanting. Everything turns on how one interprets the claim that questions about art are questions about the conventions governing appreciative judgments about artworks. The kinds of questions answered here are not questions about the role artistic conventions play in our engagement with artworks. They are not what questions about the reasons we find value these conventions in the first place. The short answer to the second kind of question is because they define the objects, events, and practices constitutive of our categories of art. But this answer won't be particularly satisfying to anyone who takes why questions seriously. My intuition is that we can appeal to dopaminergic reward systems to model the emergence of artistic value in our engagement with artworks as a how question. It is possible that anthropological and evolutionary accounts of art could give us purchase on related why questions, as might studies in cultural criticism at the humanities end of research on the arts. These are hard questions for future directions and another day, though. Notes 1 Morris, R. 1968. Third Waste Installation. Museum of Modern Art, New York, New York. Retrieved from 2 Morris, R. 1968/9. Steam Installation. Museum of Modern Art, New York, New York. Retrieved from 3 Rauschenberg, R. 1955-59. Monogram Sculpture. Modern Music, Stockholm. Retrieved from 4 Johns, J. 1961. 0-9 Painting. Tate Modern, London. Retrieved from 5 Baldessari, J. 1966-68. Tips for artists who want to sell painting. Marion Goodman Gallery, New York, New York. Retrieved from 36 William P. Seeley 6 Lewitt, S. 1977. Wall Drawing, 305 Installation. Masmoka, North Adams, Ma. Retrieved from 7 Paula, J. 1950. 1. Number 31 Painting. Museum of Modern Art. New York, New York. Retrieved from Aidan Affordance is a relation between an organism and some aspect of their environment that affords the opportunity for that organism to perform an action. For instance, chairs are artifacts that afford sitting for Homo sapiens. In this context, representational paintings afford the perception of dynamic scenes in depth, figurative sculpture affords the perception of the dynamics of animate figures, and narrative artworks afford empathetic engagement with characters by virtue of replicating critical stimulus features of our ordinary physical/social environment. 9 Johns, J. 1960. Painted bronze sculpture. Collection of the artist. C. Barnado, 1960, 185. 10 Johns, J. 1961. Painted bronze, Valentine Ale, sculpture. Kunstmuseum Basel, Basel. C. Barnado, 1960, 184. 11 C. Seeley, 2014, for a more detailed discussion of these points. 12 Picasso, P. 1937. Guernica Painting. Museo Reina Sofia, Madrid. Retrieved from 13. It is critical in this context to disentangle the notion of content from the related concept of interpretation. Interpretation is a tricky business. I take it that contextual factors influence the process of interpretation and constrain the validity of a particular interpretation on an occasion. Consider, for instance, differences in the interpretation of politically charged conceptual artworks as contemporary vehicles for social change as opposed to historical artifacts. The content of these kinds of works does not change across historical contexts. But an interpretation of the work as a live expression of current normative social issues may well be strikingly different than retrospective historical interpretations of the same work as an expression of a political movement embedded within the broader social structure of its time. The same might be said for the relationship between an artwork and an artistic movement. Surely the broad lens of history yields a different interpretation of action paintings like Jackson Pollock's than did the polemical lens of mid-century art criticism current to their time. This is not to say that interpretation is a subjective matter. Rather, interpretation must be flexibly sensitive to changes in social and epistemic context in a way that categorical judgments that constrain our understanding of the content of an artwork are not. See Dento 2001. Pollock's work is an expression of aspects of Greenbergian modernism. Facts about the flatness of its composition and the transparent roughness of his brushstrokes reflect Greenberg's attention to the formal aspects of medium and support, whatever it might have meant then or means to us now for someone to have painted that way. Chapter 3 states, People and Contexts. 3 Psychological Challenges for the Neuroscience of Aesthetics. Gary Payne and Paul J. Sylvia. The psychology of aesthetics is one of psychology's oldest fields, dating back to Fechner, 1876, and the early experimental psychologists. The early decades saw a small but interesting stream of research, for reviews, see Gordon 1909, Valentine 1913, but psychological aesthetics didn't catch fire until the emergence of Daniel Berlin in the 1960s. Berlin and his research group situated aesthetic problems within the science of experimental psychology, which both introduced aesthetics to a mainstream research community and inspired researchers to apply traditional paradigms to aesthetic questions. Although best remembered for his many contributions to psychological aesthetics, Berlin viewed his research as essentially neurological. Sylvia 2005b, 2006b. Throughout his writings, one sees a tough-minded attempt to anchor aesthetics in the neuroscience of reward. His early model, Berlin 1960, linked aesthetic preference to changes in arousal, which were generated by the reticular activating system in response to stimulus properties such as complexity, novelty, and conflict. Based on the emerging field of affective neuroscience, Holt's 1962, 1973, Berlin's 1971, 1973, 1974, later model proposed a set of interacting neurological reward and aversion systems that created affect. Psychological aesthetics and neuroaesthetics thus have a long and shared history. Research since Berlin's time has been primarily behavioral rather than biological, but like Berlin, we see these as complementary approaches. The recent rise of neuroaesthetics is an exciting development, one that promises to fulfill Berlin's vision of a model of aesthetic experience anchored in modern neuroscience. Our goal in this chapter, rather than review the vast literature on psychological aesthetics, is to isolate a handful of challenges that psychological aesthetics has grappled with since Berlin's time. By considering what psychological aesthetics has learned, neuroaesthetics can leverage past knowledge, avoid making similar mistakes, and lend insight into some problems not easily understood with behavioral methods. We will focus on the 3 challenges that we think are most pressing for modern research: the diversity of emotional reactions to the arts, the surprising individual variability in aesthetic responses to the same art objects, and the range of contexts where aesthetic experience can occur. States, People, and Contexts 41 3.1 states, the diversity of emotional response to the arts. As any teenager will tell you, feelings are complicated. The first major challenge for neuroaesthetics and an ongoing challenge for psychological aesthetics is to illuminate the wide range of emotional states that are experienced in response to the arts. Psychological aesthetics has historically concerned itself with ratings of low-intensity positive states such as liking, beauty, and pleasure. Sylvia 2009. Due to the dominance of liking in psychological studies, it is no surprise that the neuroscience of aesthetics has similarly focused on measures of mild positive states as the defining aesthetic response. Theories of emotion, however, propose a wide array of emotions: happiness, pride, interest, confusion, anger, sadness, shame, awe, and disgust, among others. Izzard 1977, Skur 2001, and all emotions are relevant to something as profoundly human as the arts. Within neuroaesthetics, it has been suggested that judgments of beauty are the cornerstone of aesthetic evaluations. Jacobson et al. 2004. Accordingly, many studies have used a single positive-negative dimension to represent aesthetic experience when analyzing how neural activation correlates with subjective ratings, such as dichotomous decisions of beauty. Selakonda et al. 2004, scales that range from appealing to not appealing. Kirk et al. 2009, and scales ranging from ugly to beautiful. Kawabata and Ziki 2004. Beauty and its related positive states are obviously important to aesthetics. Beauty is central to definitions of aesthetic experience, Gordon 1909, and to how people evaluate art objects. Augustin et al. 2012, Jacobson et al. 2004, but aesthetics research should look beyond the cluster of positive feelings to consider other aesthetic states, which we highlight below. 3.1.1 Some curious aesthetic emotions: interest in the knowledge emotions. Interest, an emotion associated with learning and exploring. Sylvia 2006b, 2008b, was one of the 2 states emphasized in Berlin's research. Many studies found that self-report scales, behavioral measures of preference and exploration, and physiological outcomes form 2 broad factors, a pleasingness factor and an interestingness factor, e.g. Berlin 1974. The interestingness factor was hard to fit into Berlin's neurological model, which emphasized pleasingness, but it remains one of the central aesthetic responses to the arts. Finding something interesting promotes attention, exploration, and learning. Izzard 1977, Tompkins 1962, and interest might be a precursor to more powerful aesthetic emotions. Markovic 2012. Interest comes about when people appraise something as both novel and complex but comprehensible. Sylvia 2005A, 2005C. Recent work has placed interest within a family of knowledge emotions, which include surprise, confusion, and awe. Sylvia 2010. The knowledge emotions are essentially metacognitive. They come about from people's appraisals of their own knowledge and expectations, and they motivate learning, viewed broadly. Several studies show that people commonly express surprise. Lutton and Schifferstein 2007, Lutton et al. 2008, 2009, confusion, Sylvia 2010, 2013, Sylvia and Berg 2011, and awe, Keltner and Hay 2003, in response to the arts. 42 Gerildane and Paul J. Sylvia Beauty Armstrong and Detweiler Bedell, 2008, sought to redefine the aesthetic experience of beauty. In their view, beauty is the exhilarating feeling that something complex, perhaps to the point of being profound, might yield an understanding. P312, not a mild pleasant state that people experience upon viewing something pretty. They theorize that this powerful aesthetic experience is rooted in prolonged, effortful processing and a goal of understanding something particularly challenging. Understanding is acquired in stages, which increases pleasure as the beholder gets closer to comprehension. They distinguish the beautiful from the merely pretty based on cognitive effort. Prettiness is facilitated by fluent processing, River 2012, but stimuli that elicit beauty thwart conceptual understanding and yet make understanding seem within reach. Beauty is conceptualized by a tripartite framework of cognition, appraisal, effect, valence and arousal, and motivation. Importantly, Armstrong and Detweiler Bedell emphasize a motivational promotion focus, which occurs when the perceiver is interested in expanding their schema, knowledge, and experience. Although not much research has examined this conception of beauty, it is clearly far from the usual use of the concept of beauty in aesthetic research, an item used to measure mild positive experiences. Awe, a powerful emotional experience that is fundamental to the arts, has received surprisingly little mention in psychological aesthetics. Nussbaum and Sylvia 2014. Keltner and Hay, 2003, described awe as a highly arousing emotion that is felt in response to vastness and the need for accommodation. Vastness comes from situations and objects that are either physically larger than the self or experientially larger than normal everyday experiences. Accommodation is the organism's ability to come to terms with the vastness of the experience. A study analyzing experiences of awe found that it was mostly felt in response to information-rich environments of nature, art, and music. Shida et al. 2007. Chills, a feeling of shivers, thrills, or goosebumps, particularly on the scalp, neck, and back is an intriguing aesthetic response. It can be evoked by anything but seems especially common when listening to music. Curiously, some people report never experiencing chills, and others report experiencing chills daily. Nussbaum and Sylvia 2014. Unlike the other states discussed here, much of the work on chills comes from neuroscience, such as studies of chills while listening to music. Blood and Zederer 2001, Salempo and Zederer 2013, and studies of the autonomic nervous system's activity during the chills response. Benedict and Kernbach 2011, Gru et al. 2007. Negative emotions. Many interesting aesthetic experiences aren't positive at all. Cooper and Sylvia 2009, Sylvia and Brown 2007. Anger, for example, is a common reaction to art that strikes viewers as states, people, and contexts. 43 transgressive. Much art does deliberately try to offend and provoke the audience, and audiences do become angry sometimes to the point of defacing and censoring art when they think someone is intentionally trying to go against their values. Disgust, another negative emotion, is a common response to art that seeks to unease the audience. The experience of disgust can be both literal, e.g. from depictions of revolting things, and metaphorical, e.g. disgust from ideas, behaviors, and values that strike viewers as morally repulsive. Shame and embarrassment, two negative emotions in the family of self-conscious emotions. Tracy and Robbins 2007, seem relevant to the arts, but essentially no research has applied them to aesthetic experience. 3.1.2 Cognitive appraisals and emotional differentiation. How can we recognize the diversity of aesthetic emotions without becoming bewildered by it? How can we understand the differences between these many states? One approach to studying diverse emotions that has been particularly successful is the cognitive appraisal theory of emotions. Lazarus 1991, Spur 2001. Appraisal theories suggest that emotions emerge from cognitive evaluations of the circumstances that people find themselves in, particularly evaluations of how what is occurring relates to their needs, preferences, goals, and abilities. Ellsworth and Spur 2003. These evaluations, called appraisals, are subjective and therefore able to account for the variations in responses to the same situation. Seymour et al. 2007. The appraisal approach has been applied to the study of aesthetic emotions and forms the basis of several theories. Armstrong and Detweiler Bedell 2008, Sylvia 2005b. Within aesthetics research, the appraisal approach has been most often applied to the emotion of interest. Two appraisals that have consistently predicted interest in aesthetic stimuli are novelty, complexity, and coping potential. The novelty complexity appraisal facilitates attention to possibly important changes in the environment. Ellsworth and Spur 2003, and the coping understanding appraisal estimates our capacity to cope with a given situation. Lazarus 1991. In the context of the arts, the novelty complexity appraisal reflects how unfamiliar, complicated, and surprising the work strikes someone. This is followed by the coping understanding appraisal, which reflects the perceiver's beliefs about his or her ability to come to understand the new and complex stimuli. This appraisal structure has been replicated for a wide range of aesthetic objects, poems, film, and visual art, indicating stability across different types of stimuli. Sylvia 2005a, 2005c, 2008a, Sylvia and Berg 2011, Sylvia et al. 2009. The value of the appraisal approach in differentiating emotions in response to the arts has been applied to differentiate knowledge and negative emotions. Confusion has been shown to be a result of a high novelty complexity appraisal and a low coping understanding appraisal. Sylvia 2010. Surprise has been shown to rely primarily on the appraisal of novelty complexity. Spur 2001. Anger and disgust have both been shown to rely on the appraisal of value congruence. Seeing something is consistent or contrary to one's values, but they are differentiated by the intention appraisal for anger. Seeing 44 Gerildane and Paul J. Sylvia something is deliberately caused by someone, and the pleasantness appraisal. Seeing something is inherently aversive, for disgust. Sylvia and Brown 2007. Another important finding using appraisals is the dissociation between interest and pleasure. Turner and Sylvia 2006. When people viewed a set of pleasant and disturbing paintings, ratings of pleasantness and interest were unrelated. Pleasantness and interest may overlap in many and perhaps most situations, but pleasantness isn't necessary for something to be interesting. A person may thus find an artwork to be displeasing but still be aesthetically engaged with it. The distinction between pleasantness and the other emotions we have discussed is less subtle but just as important. Things needn't be pleasant or beautiful for most emotions to occur, so judgments of beauty alone aren't enough to capture and differentiate aesthetic experiences. 3.1.3 What does this mean for neuroaesthetics? The key message, one that applies equally to the psychology and neuroscience of aesthetics, is that aesthetic experiences are much broader than judgments of beauty and preference. People seek and experience powerful and diverse feelings. Such states can be both positive and negative, and importantly, they can be independent of preference and beauty. Yet they are united by making the perceiver feel moved, creating a special subject-object relationship that may be the quintessential aesthetic experience. Evidence for the benefits of a more expansive approach to aesthetic emotions comes from a recent study in neuroaesthetics, in which a novel MRI assessment was used to find step-like increases in activity in frontal regions of the brain, including the default mode network. Vessel et al. 2012. Participants were asked to rate a series of images based on how much it moved them, and were told to focus on the powerful, pleasing, and profound. The step-like activation in the default mode network for artworks that yielded only the highest rating is of particular interest because this region is associated with self-referential mentation, particularly memory retrieval and envisioning the future. Buckner et al. 2008. This finding might indicate the special subject-object relationship where art elicits introspection and contemplation. Further, it was found that post-scanning ratings of awe were related to unique activation, differentiating awe from other types of emotional experiences. Bessel et al. 2012. This study is a good model for neuroaesthetics research that attempts to look at more powerful, personal, and enduring aesthetic emotions. The appraisal approach has proved useful in distinguishing aesthetic states and could easily be implemented in neuroaesthetics research. Measuring key appraisals along with emotion ratings could identify activation associated with these evaluative judgments and clarify some of the inconsistencies in findings based on preference ratings. It is important to note that some neuroaesthetic studies have chosen stimuli that were above the mean in complexity. Selakonda et al. 2004, 2009. These ratings, however, were done by a separate sample, and as we have seen in our research, complexity and other appraisals are in the eye of the beholder, and therefore, should be measured individually whenever possible. States, people, and contexts 45 3.2 people. The challenge of individual differences in aesthetic experiences, individual differences in emotional responses are the rule, not the exception. Few things evoke the same feelings in everyone. Seymour et al. 2007. For the arts, then, we would expect massive variability in how people respond to the same things, and we do see this in everyday life. The challenge, then, is to understand the basis behind these differences, to identify what explains why people experience art so differently. The theoretical and practical value of combining experimental and differential methods has been stressed for a long time, Cronbach 1957, and recently been reiterated, particularly for the neurosciences, Kanai and Rees 2011. The idea of moving away from the general in lieu of the particular has also been raised as a challenge to neuroaesthetics, Nadal and Pierce 2011. Given the small sample sizes that are inherent in neuroaesthetic research, researchers should use the literature on individual differences to select, study, and compare thoughtfully chosen participants. Many traits predict variability in aesthetic experience, but two openness to experience and expertise in the arts are by far the most important. Different standings on these variables predict different intensities and kinds of aesthetic experience. If studying powerful aesthetic emotions is a goal of neuroaesthetics, then recruiting participants who are more likely to experience such emotions becomes important. Additionally, an individual differences approach to neuroaesthetics can also give insight into these constructs by illuminating the different ways aesthetics is processed neurologically by different people. 3.2.1 Openness to experience. One of the dimensions in the five-factor model of personality. McCrae and Costa 1999. Openness to experience is fundamental to aesthetic appreciation and creativity. Feist 1998. Sylvia 2012. Openness includes the subtraits of fantasy, having a vivid imagination, aesthetic sensitivity, appreciating art, nature, and beauty, feelings, being sensitive to the subtleties of inner emotional states, actions, being open to trying new things and visiting new places, ideas, having high intellectual curiosity, and values, being willing to re-examine values. Openness is the most heterogeneous of the five factors, and disagreements about its nature might be the most contentious. Deng et al. 2012, McCrae 1994, McCrae and Suden 2009. One recent model of openness to experience, the O/I model, divides it into two facets, openness and intellect. Deng et al. 2007. The openness facet is theoretically related to aesthetic sensitivity, creativity, and imaginativeness. The intellect facet, in contrast, is linked to fluid intelligence, vocabulary knowledge, and an intellectual approach to life. Several studies have found evidence for this carving of openness to experience. For example, openness and intellect diverge in how they predict performance on creativity and intelligence tasks. Nussbaum and Sylvia 2011a, implicit and explicit learning, Kaufman et al. 2010, and major creative achievements, Kaufman 2013. 46 Grilfane and Paul J. Sylvia. Openness to experience has consistently predicted aesthetic appreciation and engagement in the arts. Openness was found to predict engagement in aesthetic activities such as reading, painting, visiting art galleries, and valuing the arts, McManus and Fernham 2006. Additionally, it has been found to predict higher liking and interest in several different forms of visual art, with particularly strong associations with abstract forms of art. Fain and Tiliopoulos 2012, Feist and Brady 2004, Rawlings 2003. Finally, in a large-scale population study, N equals 91,692, openness was found to be the strongest predictor of art appreciation and artistic activities, Chamorro Pre-Music et al. 2009. These findings indicate that people higher in openness enjoy their experiences with art more, have more positive attitudes towards the arts, and engage in behaviors that expose them to the arts. Apart from liking and enjoying art more, people high in openness are more likely to have powerful and unusual emotional experiences in response to the arts. One of the items on the openness scale of the Neo Personality Inventory asks participants about their tendencies to experience chills in response to poetry and the arts. A cross-cultural study by McCrae, 2007, found that in 50 out of 51 cultures, the item asking about chills had one of the highest item total correlations with the total openness to experience scale. For the whole sample that combined all 51 cultures, the chills item had the highest item total correlation of all the items. McCrae concluded that the experience of aesthetic chills was a universal and central marker of the openness trait. In our own work, we have found that openness to experience is the most common predictor of how often people reported experiencing chills from listening to music. Nussbaum and Sylvia 2011b. People high in openness were more deeply engaged with music in many ways, e.g. going to concerts, playing an instrument, and this deeper engagement mediated the effect of openness on chills. In other words, we split openness to experience into the O and I facets, and when people were asked to report how often they got chills in responses to the arts, openness but not intellect emerged as an important predictor. Sylvia and Nussbaum 2011. Moving beyond chills, openness to experience predicts other strong aesthetic experiences. For example, there is a strong association between openness and self-reported experiences of awe in everyday life. Shida et al. 2006. When people rated how often they had a range of aesthetic experiences in response to whatever domain of the arts they encountered most often, the openness of /I facet strongly predicted how often people reported experiences such as wanting to cry and feeling moved, touched, and absorbed. Sylvia and Nussbaum 2011. Finally, those scoring higher on the openness of /I facet experience a stronger relationship between interest and aesthetic fascination, indicating greater emotional reactivity to interesting art. Fain and Tiliopoulos 2013. 3.2.2 Knowledge, expertise, and training. Expertise in the arts is the second big individual difference variable in aesthetic experience. Some people know an incredible amount about the arts, others have a more casual knowledge of art, and many people know little. Expertise knowledge in the domain of the states, people, and contexts 47 arts gained through training and formal study moderates virtually everything, and it is currently a hot topic in psychological aesthetics. Compared to novices, experts in the arts evaluate their subject using different dimensions. Heckert and Van Moeringen 1996 think about art using concepts that are more formal and abstract. Parsons 1987 and view visual images differently, according to eye tracking studies. Locker 2006. Most relevant to our purposes, however, are emotional differences. Experts and novices have different aesthetic responses to the arts. Expert-novice differences in emotional reactions to the arts are robust effects that are easy to find, e.g. Letter et al. 2012, Locker et al. 2001, Millis 2001. One common finding is that experts, relative to novices, enjoy work that is more complex, abstract, and non-representational, e.g. Heckert and Van Moeringen 1996. Experts are also less likely to find complex works confusing, Sylvia 2013, Sylvia and Berg 2011, and are more likely to find them interesting, Axelson 2007, Sylvia 2006a. Expertise is measured in a handful of straightforward ways. One approach is to classify people as experts or novices based on tangible achievements and attainments, such as working in the arts, having a college major or degree in the arts, or having taken classes in the arts, e.g. Honstra et al. 2013. Some research combines attainments with interest in the arts. People must have both extensive attainments and indicate an elevated interest in the arts to qualify, e.g. Locker et al. 2001. Another approach measures people's knowledge about the arts. Smith and Smith's 2006, Aesthetic Fluency Scale, for example, presents people with a list of figures and topics in art history. For each one, people are asked to rate how much they know about it using a scale that ranges from 0, I have never heard of this artist or term, to 4, I can talk intelligently about this artist or idea in art. The scale is based on the simple notion that experts know more than novices, so asking for simple knowledge judgments will catch most of the variance associated with expertise. This scale has been used in many studies and works quite well. Dual ETAL 2011, Sylvia 2013, Sylvia and Verona 2009, Sylvia and Nussbaum 2011. The basic method lends itself well to modified versions, such as extensions to the domains of film, writing, and the decorative arts. Sylvia 2007, Sylvia and Berg 2011. It should come as no surprise that expertise and openness to experience overlap. Experts in the arts are much more open to experience than novices, consistent with the role of openness in aesthetic sensitivity and creativity. In one study of college students, scores from the aesthetic fluency scale strongly predicted openness to experience, beta equals 0.55, Sylvia 2007. Openness, a personality trait, and expertise, acquired crystallized knowledge, are clearly different, but being high in openness to experience provides the interest and motivation needed to develop expertise in the arts. 3.2.3 What does this mean for neuroaesthetics? Individual differences influence the intensity and quality of emotional responses to the arts. Openness and expertise are particularly involved in more powerful and transcendent states that define aesthetic experience. The mechanisms for these differences are not totally clear, but early evidence suggests that people high in openness and art expertise are more 48 Grilfane and Paul J. Sylvia likely to approach art with the view of expanding their lives, are less likely to experience confusion in the face of complexity, and are more likely to have powerful emotions in response to the arts. One clear implication for neuroaesthetics concerns sampling. Neuroscience research has much smaller samples than behavioral research, and individual differences can wreak havoc in a small sample. If nothing else, it is important to measure personality and expertise to describe what the sample is like. More fruitful, however, would be to select participants based on individual differences. One approach is to select the people for whom intense aesthetic reactions are common, such as people high in openness and expertise. Another is to select extreme groups based on these variables, such as picking people low and high in openness. By expanding the variance between people, this design increases statistical power, which is always handy for small sample methods. Regardless of the specific implications, paying more attention to individual differences can help with the problem of decontextualizing participants and the differences that exist between them. Nadal and Pearce 2011. 3.3 Contexts. The diversity of aesthetic objects and environments. One of Berlin's legacies is an emphasis on controlled laboratory experiments with carefully selected stimuli. The contexts of aesthetic experience, the things people encounter and the places in which they encounter them, are thus largely ignored. We know a great deal about aesthetic experience as it happens in an unfamiliar room in response to unfamiliar images that someone else picked. We know much less about what aesthetic experience involves in people's natural environments. We thus see the problem of context as having two sides. The first is the diversity of aesthetic objects. Things that are easy to study experimentally, such as visual images, have been widely studied, whereas things that are complicated and inconvenient, such as narrative text, film, and theater, have not. The second is the diversity of aesthetic contexts. People experience aesthetic objects essentially everywhere at home, in museums, in their cars, on smartphones, and anywhere people come into contact with ideas and objects with an aesthetic purpose. Few studies, however, have taken arts research out of the lab and into the real world. 3.3.1 Varieties of aesthetic objects. Some kinds of art are more convenient to study. Visual art and music, perhaps the two most widely studied domains, lend themselves well to lab paradigms. They can be presented using inexpensive equipment. Researchers don't need special facilities or personnel. Aspects of the presentation can be precisely determined, and it doesn't take much time in an experiment to show pictures or play music. For neuroimaging research, visual art and music are the most scanner-friendly, given current technologies. It is easy to show pictures or play music presenting a lengthy text, short movie, or a stage play present more or less obvious challenges. States, people, and contexts. 49 are senses that psychological aesthetics has taken a more expansive approach in recent years, which has seen more interest in a wide range of art domains. In narrative text, recent years have seen many new papers along with a new journal, Scientific Studies of Literature. Likewise, many interesting papers have appeared recently on literature, theater, music, and film, and empirical studies of the arts and psychology of aesthetics, creativity, and the arts, the field's two leading journals. Being researchers who focus on lab-based studies of visual art and music, we can appreciate the effort involved in extending the field to new areas. Some researchers are moving outside of the traditional fine arts entirely. One notable program of research examines the aesthetic experience of designed products in both the lab and in natural environments. Demir ETAL 2009, Ludden ETAL 2008, 2009. In a similar vein, Whitfield has argued for the study of mundane aesthetics. Whitfield and DeStefani 2011. He has used designed objects as contexts for evaluating competing models of aesthetic experience. Whitfield 1983, Whitfield and Slatter 1979, and recent work has focused on how people make common aesthetic decisions, such as choosing paint colors for their interior walls. Whitfield and DeStefani 2011. An historic line of work by Berlin and his collaborators examined aesthetic responses to architecture and the built environment. Ustendorf and Berlin 1978A, 1978B, and an emerging line of research explores the aesthetic experience of images of space. L.F. Smith 2014. 3.3.2 Varieties of aesthetic locations. People encounter aesthetic objects in so many places. They listen to music at concerts, view art in museums, experience architecture as they amble through the built environment, experience nature as they wander through the natural environment, and interact with designed products from clothes to watches to cars everywhere. The diversity of aesthetic environments will be harder to analyze. Research is much easier to do in a lab, especially when it involves massive magnetic machines. Nevertheless, researchers have made some intriguing progress in studying aesthetic experience in the world that exists beyond the laboratory doors. An emerging body of work has applied experience sampling methods, ESM, to aesthetic experience. Such methods assess people repeatedly in their natural environments. By randomly sampling people's everyday experience, researchers can understand how often things actually happen, capture experiences as they occur, and study things that can't be studied using static, one-shot assessments, such as the variability and volatility of people's experiences. Connor ETAL 2009, Heckner ETAL 2007. ESM research has been most commonly applied to music. Randomly sampling a person's day is a good way to estimate how often people listen to music and what kinds of emotions they typically experience when doing so, e.g. Jocelyn ETAL 2008, Sloboda ETAL 2001. Recently, our group has used ESM to study how often people get chills when listening to music and what kinds of contexts promote chills, Nussbaum ETAL 2014, as well as why some people only rarely listen to and enjoy music, Nussbaum ETAL 2015. In another 50 Grilfane and Paul J. Sylvia project, Beatty ETAL 2013, we have examined how often people hear inner music, imagine music when none is playing, and whether it is typically an aversive experience, as stereotypes about earworms and stuck song syndrome would suggest. Telleris 2008, Levitin 2006. In psychological aesthetics, there is a small but excellent body of work that studies the experience of art within museums, e.g. Hope 2003, Mastandrea ETAL 2007, J.K. Smith 2014. These studies are both correlational and experimental, and they have examined a range of interesting problems, such as how long people spend looking at art, Smith and Smith 2001, what people tend to look at, Heidenreich and Toronto 2011, and how the experience of a reproduction differs from the experience of an original, Walker ETAL 2001. The natural extension, as technology advances, is to add biological measures to assess experience in natural environments. Ambulatory brain imaging won't be practical and widespread for some time, but ambulatory measures of the autonomic nervous system are relatively inexpensive and easy to use. One outstanding example of the use of ambulatory autonomic physiology is a project by Chater and colleagues, 2012. In this research, participants wore a glove device during a visit to a fine art museum. The device tracked their movements through the museum and provided markers of sympathetic and parasympathetic activity. The researchers could thus link physiological activity to aspects of the art, e.g. a painting's fame or intensity, and to participants' self-reports. Trondle and Chater 2012. Other options include ambulatory impedance cardiography, Cybulski 2011, which uses electrodes placed on the chest and back to measure the electrical and mechanical activity of the heart, Thayer ETAL 2008. From this, it can assess the influence of the sympathetic and parasympathetic branches of the autonomic nervous system by calculating measures of the heart rate, force of contraction, e.g. the cardiac pre-ejection period, a measure of sympathetic influence, Telsey 2012, and variability, e.g. heart rate variability, a measure of parasympathetic influence, Segerstrom ETAL 2012. Ambulatory impedance devices are small, comfortable, and discreet, so they hold great potential for measuring biological aspects of aesthetics in everyday public environments. 3.3.3 What does this mean for neuroaesthetics? The challenge of contexts presents the greatest difficulty for both neurological and behavioral research on aesthetics. For many neuroscience methods, visual imagery and music are the only practical aesthetic domains. Certain methodological requirements, such as precise time linking of events and measurements and the practicality of what people can perceive while lying in a scanner, mean that many kinds of dynamic domains are out of reach for now. Likewise, ambulatory neuroscience methods are in their infancy, so extending neuroaesthetics into museums and recital halls is far off. At the same time, some exciting options for ambulatory central imaging are looming on the horizon for basic research, and options for ambulatory autonomic nervous system assessment are practical and relatively affordable. Cybulski 2011. For now, then, the challenge of context is something still at the back of the field's mind, something to take up as the field finds new methods, technologies, and insights. 3.4 Conclusion These are exciting times for the scientific study of the arts. Based on who we see at conferences and what we see published in journals, the field is attracting a diverse pool of young talent and an intriguing range of topics and methods. The emergence of neuroaesthetics is one sign that the science of aesthetics is maturing. In this chapter, we offered some food for thought based on the experience of psychological aesthetics. The past decades of research using behavioral methods has revealed a few core issues: the diversity of aesthetic states, the diversity of individual responses, and the diversity of aesthetic contexts. These are challenging problems that neuroscience approaches to aesthetics should both confront and tackle. In some cases, neuroaesthetics can learn from the mistakes of behavioral work, such as the perils of defining aesthetic experience solely in terms of positive states. In other cases, we expect that neuroaesthetics can solve some problems that are hard to crack with psychological methods, such as the nature of obscure states like chills and awe. In either case, we are curious to see what the future holds for the fledgling field of neuroaesthetics. 4.1 Introduction Strange behaviors. Among the puzzling things that humans do which at first sight have no apparent biological use are many of those activities we subsume under the concept of culture. For example, humans spend hours in theaters and concert halls, and they also visit art exhibitions, which often require traveling and other costs. In more abstract terms, regarding art, people spend time in quiet spaces and look at human-made 2- or 3-dimensional structures that remain unchanged, delivering a stable flow of rather invariable sensory stimulation. In the present chapter we discuss the study of processes involved in such behaviors, specifically in art appreciation, and how researchers can measure psychological processes and states of aesthetic appreciation by using behavioral and psychophysiological methods. The object of our studies, the consumption of art by mankind, is quite old. Available evidence suggests that art is a unique human feature. Davies 2012. Examples of prehistoric art range back at least 80,000 years. Thus, along with weapons and tools, artworks are among the oldest human artifacts. Although we know little about how the early artworks were perceived, and we have no evidence for the particular kinds of receptor perspectives involved, Dutton 2009, artistry is deeply embedded in our evolutionary past. For many people today, at least in many Western cultures, going to a museum is a common behavior, or some even a frequent behavior. Nevertheless, the concept of a museum as we know it today is a relatively new invention. Shiner 2003. The Capitolian Museum that opened in 1471 in Rome can be regarded as the first modern museum. Independently of whether cave paintings are seen as ancestors of the modern concept of museums, or whether museums are classified as a recent development in history, the existence of art raises the question of what kind of behavior the perception of art is, and what kind of experiences it yields. Art's appeal might be due to various distinct possibilities. Psychology of the arts has focused on the quality of experiences that explain why this behavior is demonstrated. Letter ETAL 2004. In this vein, artworks and exhibitions represent an unquestioned aesthetic value to visitors, and promise exciting, enlightening, or uplifting experiences. This relates to the most often assumed explanation of aesthetic behavior, that art affords hedonic states of positive experiences of beauty, pleasure, or the sublime. 58 Helmut Letter, Gernot Berger, and David Grieber. However, there are various examples of contemporary art exhibitions for which such simple, straightforward effects can hardly be true. For example, consider Teresa Margoli's contribution to the Mexican Pavilion at the Venice Biennale in 2009, named What Else Can We Talk About? In Margoli's installation, family members of homicide victims of the Mexican drugs war cleaned the floors of a Venetian palace with water that was taken from the burying grounds of the victims. This could not be said to offer the viewer a first-hand pleasurable experience. Thus, at least when it comes to contemporary art, alternative explanations of the appeal of art should be discussed. Art can promise interesting, arousing, sometimes challenging experiences, by presenting new, innovative, and even provoking artworks, which do not explicitly aim to display the beautiful or the sublime. However, these artworks might receive their appeal from situations that require some resolution, that is, perceivers are trying to understand and make sense of what is displayed by the artwork and intended by the artist, similar to the solution of a cognitive puzzle or the resolution of visual ambiguity. Such processes might be self-rewarding. Letter ETAL 2004. This also relates to explanations that stress social functions of art. Artists adopt a certain view of the world, they often express a specific attitude. Consequently, early psychological approaches emphasize that the perceiver has to be able to empathize with the artwork or the artist. See Curry 2011, for a comprehensive discussion. Thus, art also allows for practicing playfully and learning to perceive, interpret, and exchange viewpoints and opinions. DeSantiaki 2007. Related to this explanation, evolutionary approaches argue that art making an appreciation serves an important ritualistic function that enhances social cohesion. Chaturji 2011, p56. Psychological analysis of art is usually directed towards an inner perspective, such as the psychological states and processes during perception of art. In this chapter we aim to address two issues. First, we discuss how psychology understands the behavior of perceiving and enjoying art. Second, we deconstruct the experience of art into different components and discuss how experimental aesthetics, and particularly its use of psychophysiological measures, provides insight into the complex processes during aesthetic receptions of visual art. 4.2 How do psychologists understand aesthetic experiences of art? Psychology aims to describe, explain, and, through scientific understanding, predict human behavior and experience. The focus of most psychological theories is a kind of interview of a person, James 1890. In this respect, psychology of aesthetics aims to determine the processes that take place in a perceiver, in order to explain what he or she likes aesthetically. Fechner, 1876, in his Forstschulder Ästhetik expressed this in the following way: in considering the aesthetic effect of anything upon us, we do not only think about the concepts under which it can be subsumed, and its categorization within such a system, although such questions need to be asked. However, the most interesting and important question has to be, why is something liked or disliked? The answer to this question can only be found in the specific laws aesthetic appreciation 59 relating to liking and disliking, and in the laws of obligation, in just the same way that the particular movements of physical objects are explained by the laws of motion, and by the reasons and purposes of those movements. Movements cannot be explained alone by naming concepts or categorizing into different types of movement, but require precise laws of motion, whilst the purposes of the movements are also taken into account. Conceptual explanations in aesthetics will therefore be nothing but an empty framework, until they are confirmed by proper explanatory laws. Translation by letter and Flames, see letter, 2014, p. 117. Fechner founded the field of empirical aesthetics with his Forstschulder Ft. 1876. In this approach he distinguished bottom-up, stimulus-driven, from top-down, cognitive-driven, approaches and anticipated the interplay of these approaches during aesthetic receptions. This is much in accordance with what psychology today has identified as happening within a person when he or she experiences a work of art. Letter ETAL 2004. Fechner's empirical studies were clearly concerned with aesthetic reception, not production. He presented the first laboratory studies regarding the principle of the golden section in rectangles, according to which a ratio of 1 to 1.618 should be particularly beautiful, and conducted a first field study in a museum by comparing the appreciation of two versions of Holbein's Madonna, exhibited in the Semper Gallery in Dresden. Interestingly, although Fechner made aesthetics one of his two main research topics, in addition to psychophysics, the progress of empirical aesthetics throughout the 20th century was surprisingly slow. Mainstream psychology had a stronghold in perceptual studies, but other topics of clinical, social, and basic processes in perception, like attention and thinking, became more dominant themes. There were exceptions, such as Karl Buehler's 1913 approach to Gestalt psychology, which very explicitly starts with a reference to art history. However, only after the influence of behaviorism subsided did experimental aesthetics experience a revival, owing mainly to Berlin's biological arousal approach in the 1970s. Since the cognitive revolution, the information processing concept has guided the study and understanding of human behavior for half a century. As a result, cognition, thinking, and internal representations are common to many psychological theories. The information processing model developed by Letter and colleagues, 2004, and Cheturgis, 2003, neuropsychological model, are two examples of this. In both models, the aesthetic experience is defined as a sequence of an interaction between information processing stages. Figure 4.1 shows Vartanian and Nadal's, 2007, integration of both models. Cheturgi, 2003, distinguished aesthetic decisions and emotional responses as outputs of his model. Both are the result of processing stages of early and intermediate vision, a representational domain, and are modulated through attention. Letter and colleagues, 2004, model aims to explain similar outputs, aesthetic judgments, and aesthetic emotions. It proposed 5 information processing stages that explain how an aesthetic experience develops from perception of an artwork to its interpretation and evaluation. Most of this model is concerned with processes that are not directly visible, they represent inner states, and constitute what informally would be called thinking. According to the information processing assumption, cognitive processes form representations and change psychological and physiological states in the person. For example, the combination 60 Helmut Letter, Gernot Gerger, and David Breber of text and image in Magritte Slaughter these and day images, one an image of a pipe, and the text Sesines pa and pipe, this is not a pipe, creates a perceptual representation of image and words that are instantly seen as contradictory. However, by means of interpretation the perceiver might resolve the seeming contradiction by realizing that the pipe is not a pipe, but an image of a pipe, and that images can represent an object, but images aren't objects. This way, due to cognitive processes, a state of resolved ambiguity replaces a state of ambiguity. In the model developed by Letter and colleagues, 2004, these cognitive processes are also seen as eliciting changes in emotional states, mainly as a consequence or byproduct of the various cognitive activities. See also Letter 2013. Thus, an art experience is a complex episode, consisting of an interaction between an object and a perceiver, and the interplay of cognitive as well as emotional processes. See Figure 4.3. The focus on the recipient's individual states might be due to the proximity and relatedness of the research programs with the field of perception. From the beginning, perception was a focus for the new discipline of empirical psychology. The early works of Helmholtz-Orville developed research approaches to human perception with high experimental vigor. If the goal of the method subsumed under the heading psychophysics was to understand scientifically the relation between the external world and its mental representation, then perception was the natural place to start. Throughout the 20th century, expertise and knowledge about perception increased alongside technological developments in image presentation and manipulation. With these developments, the complexity of research programs in psychology increased by the consideration of more complex visual arrays, such as artworks. As a consequence, today's psychology demonstrates an increased interest in the arts. Moreover, the scope has also broadened through the integration of various methods, comprising experimental, cognitive behavioral studies as well as psychophysiology and brain research. The combination of an outer psychophysics how object features affect inner states, and the relation between inner states and physiological changes, termed inner psychophysics by Fechner, pretty much determines the current program of empirical aesthetics. Figure 4.1 combination of models of aesthetic experience. Adapted from Vartanian and Nadal 2007. Stimulus early vision intermediate vision attention decision emotional response representational domain aesthetic emotion aesthetic judgment cognitive state evaluation active state output perceptual analysis implicit memory explicit classification cognitive mastering continuous active evaluation input stimulus aesthetic appreciation 61 4.2.1 psychological methods empirical psychology faces the problem that most of the cognitive and emotional processes it posits are not directly observable, and they take place in very fast succession. These successive processes are usually not even directly accessible to consciousness, thus they are difficult to report. However, based on theoretical considerations, a systematic variation of independent variables and measurement of the outcome by deploying one or more dependent variables allows us to infer these processes from observations and reporting. In experimental aesthetics, most commonly only behavioral measurements are used as dependent variables, but due to technical advances in recent decades these measurements are being complemented by psychophysiological methods. Regarding behavioral measurements, aesthetic evaluations are very often measured by preference decisions. These can be given using forced choice preference tasks or Likert scales measuring liking or preference. The scale how much do you like this is frequently used, but must be seen as a somewhat vague and very general measure of aesthetic evaluations. Letter ETAL 2005. The questions about how much an object is preferred, how strongly it evokes an aesthetic experience, or how beautiful it is, can also be posed. Interestingly, different object classes differ due to the dimensions that are associated with their aesthetic evaluation. Augustin ETAL 2012. This should be considered in experiments. Psychophysiology provides an interesting improvement to an extension of the behavioral approach, as it allows testing hypotheses associated with physiological correlates. Physiological responses are closely linked to inner states. Some of the psychophysiological methods, e.g. EEG, electroencephalography, MEG, magnetoencephalography, allow the tracking of changes in processes in real time as they have very high temporal resolution. Additionally, psychophysiological measures of the peripheral nervous system function, such as electrodermal activity, EDA, heart rate, HR, facial electromyography, facial EMG, and pupillometry complement the experimental repertoire for psychologists and can contribute to a deeper understanding of psychological processes. See Figure 4.2. Regarding EDA, one commonly used measure is skin conductance, which records how well the skin conduces current flow in between a pair of skin electrodes. As sweat secretion increases, due to sympathetic activation, so does skin conductance. Both slow, tonic, changes in skin conductance level, SCL, and fast event-related, phasic, skin conductance responses, SCR, can be interpreted as physiological indexes of arousal. SCR increases with stimulus intensity, regardless of whether it has positive or negative valence, e.g. Bradley ETAL 1990. In contrast to EDA, facial EMG can be used to measure responses associated with emotional valence because facial muscle activity is crucial to the expression of emotions, Ekman ETAL 1980. Facial EMG can detect subtle changes in facial muscle activity related to emotional processing, even if no overt changes in facial expression are visible. The musculus sigmomaticus major, which raises the corner of the mouth and causes smiling, and the musculus corrugator supercilii, which draws the eyebrows downwards while frowning, are reliable indicators of affective processes. Whereas effectively positive stimuli listed in 62 Helmut Letter, Gernot-Berger, and David Brewer increase in zygomaticus muscle activity, effectively negative stimuli increase corrugator muscle activity. Bradley et al. 2001, Dimmert and Carlson 1997. These changes are usually in accordance with self-reports of subjectively felt emotions. Dimmert 1988. One should note that facial EMG is also sensitive to changes in cognitive processing. Spur and Eldring 2007. For example, a higher cognitive load leads to stronger musculus corrugator supercilii activation. Leshner et al. 2008. Pupillometry, the measurement of pupil dilation and contraction, is another psychophysiological measure that can be applied to understand processes in aesthetics. Pupil size is controlled by the iris sphincter and the dilator muscles. The former is innervated by the parasympathetic nervous system, the latter by the sympathetic nervous system. Although pupil size variation mainly owes to changes in luminance, the pupillary light reflex, it is also associated with changes in arousal. Bradley et al. 2008, and cognitive load, e.g. Ling et al. 2012. Highly arousing pictures elicit an increase in pupil dilation regardless of stimulus valence. Bradley et al. 2008. High cognitive loads while processing visual and auditory stimuli increases pupil diameter and decreases light reflex. Kahneman and Beatty 1966. Steinhauer et al. 2000. Pupillometry is usually measured with eye tracking systems. Such systems also allow inferences about spatial, where, and temporal, when and how long, eye movement characteristics of information intake during visual exploration. Facial EMG pupil size emotion cognition and emotion eye movements brain activity O2 heart rate arousal electrodermal activity body posture respiration. EEG cognition and emotion figure 4.2 illustration of the various methods that can be used to find correlates of the inner states of a person. Aesthetic appreciation 63 during the last decade. Brain activity underlying aesthetic experiences was examined using methods such as electroencephalography, EEG, magnetoencephalography, MEG, and functional magnetic resonance imaging, fMRI. Electrical potentials of neurons produce electric and magnetic fields that can be measured from outside the skull. EEG electrodes attached to the scalp record the electrical activity. The highly sensitive magnetometers used in MEG measure the magnetic fields. EEG can be used to measure different frequency bands of neural oscillations associated with specific psychological states. Alternatively, more specific psychological processes can be analyzed with the event-related potential, ERP, technique, which averages EEG responses for a specific time-locked event. In comparison to other brain imaging techniques, EEG and MEG have the advantage of a high temporal resolution. Functional MRI, on the other hand, has a high spatial resolution. The demand for oxygen due to the increase in the activity of specific brain regions raises the regional cerebral blood flow. Functional MRI detects these changes in blood oxygenation level and thus provides an indirect measure of brain activity. These techniques are not restricted to local measures, thereby enabling the identification of networks of brain regions involved in aesthetic processing. Taken together, fMRI is suitable for testing assumptions regarding the location and involvement of brain processes, while EEG and MEG shed light on temporal characteristics within a fraction of a second. Facial EMG, measures of EDA, and pupillometry are especially useful to test overt and subtle effective responses. Studies using these psychophysiological methods have corroborated results from behavioral studies and have revealed new insights regarding the components and processes involved in art experience. Figure 4.3 Components of an aesthetic experience. Higher order thinking, emotion, perception, artwork, knowledge. Extra info, content, style 64 Helmut Letter, Gernot-Berger, and David Brewer 4.3 Components of aesthetic experience of art, behavioral and physiological approaches. Psychological theories of aesthetic experience disentangle the experience into distinctive processing stages, as noted earlier. Hereafter, we use examples concerned with some of the components in order to illustrate how their role in aesthetic episodes and art appreciation can be addressed using behavioral and psychophysiological methods. Figure 4.3 illustrates an aesthetic episode and the components that we consider in the next paragraphs. We discuss how contexts enable aesthetic processing. We study early perceptual processes including the important stages of style or content processing, and how knowledge and expertise, as well as emotion, shape aesthetic experiences from art. Regarding these components, we present findings about the processes involved by putting the emphasis on scientific studies that combine behavioral and physiological methods in their investigations. 4.3.1 The role of context. The aesthetic experience is often associated with a specific context. Such contexts can be established by pre-classifying an object as art. This is accomplished by displaying the object in a museum or by being asked to evaluate it aesthetically in the laboratory. An aesthetic context encourages the perceiver to adopt what Kupchak and Laszlo, 1992, called an aesthetic attitude, and it provides a necessary but not sufficient precondition for aesthetic experiences. Letter et al. 2004. Aesthetic experiences are then viewed as a special state of mind qualitatively different from those summoned by everyday experiences. Markovic 2012. Thus, context is a defining feature of aesthetic experiences. Many famous artists played with such contextual frames by placing everyday objects in an aesthetic context. See, for example, Marcel Duchamp's Fountain, 1917, which is a urinal, 2 Andy Warhol's Brillo boxes, 1964, 3 or Beauty's blocks of fat, 1968, 4 displayed in art museums. Indeed, seeing a urinal as an exhibit in a museum might lead to a different experience to seeing a urinal when visiting the restroom, but how do contextual cues change our aesthetic experiences? Contexts exert influence on our experience via several different routes. Critically, aesthetic experiences usually take place within rather safe environments, Frieda and Scram 1995, which pose no risk to the health and well-being to the individual. In such a context, everyday concerns can be suppressed, Kupchak and Winston 1996, allowing the individual to focus attention on the object, and to engage in an evaluative processing style of thought. Letter et al. 2004. Artists and art curators seem to be well aware of this. O'Doherty, 1976, characterized galleries as white spaces where the outside world must not come in. Everyday stimulus processing, on the contrary, is pragmatic and goal-oriented. In order to secure well-being, perception usually ensures successful identification of an appropriate reaction to various objects in the visual field. In aesthetic processing, this immediacy of generating unambiguous representations in goal-directed actions is far less pronounced. Given that aesthetic contexts reduce pragmatic and motivational considerations, the perceiver is allowed to enjoy rather ambiguous state when seeing an aesthetic appreciation 65 artwork, Jacobson Letter 2009. Indeed, artists produce works of art not just for the sake of mere representation of an object, they also exploit stylistic and formal properties in their artworks to provide the viewer with an engaging viewing experience. Pablo Picasso's Cubist paintings, René Magritte's often semantically ambiguous paintings, or in the case of abstract art, paintings devoid of any representational content, are all examples of artworks exploiting such stylistic and formal properties. In addition, an aesthetic context might be marked by certain expectations, promising aesthetically pleasing and cognitively challenging experiences when looking at art. Letter et al. 2004. It is assumed that an aesthetic context encourages an evaluative processing style. Kupchak and Winston 1996. Letter et al. 2004. In a series of experiments, Jacobson and colleagues directly tested this assumption. Participants evaluated abstract patterns in either an aesthetic task, is this stimulus beautiful, or in a pragmatic or at least non-aesthetic task, is this stimulus symmetrical, while physiological brain responses were recorded employing EEG, Jacobson and Hopel 2003, or fMRI, Jacobson et al. 2006. An aesthetic context led to a strong right hemisphere lateralization of an ERP component called delayed positive potential, LPP. The authors interpret this lateralization as reflecting an evaluative style of processing in aesthetic contexts, because the LPP is increased for stimuli of positive and negative valence, Cuthbert et al. 2000, and is associated with enhanced attentional processing for motivationally salient stimuli, Papke et al. 2012. Jacobson and colleagues, 2006, used fMRI to show that an aesthetic context elicited stronger activity in frontal networks including the ventral prefrontal cortex, BA45/47, and the frontal-median cortex, BA10/9. These brain regions are linked to evaluative judgments of persons and actions. Activation of a similar region of the BA10 was also reported by Kupchak and colleagues, 2009, in a study where artworks had to be contemplated in either an aesthetic, focus on colors, tones, composition, and feelings elicited by the artwork, or pragmatic, focus on what is depicted and follow the visual narrative of the artwork, context. Activation of BA10 is consistent with its role in top-down control of cognition, shifting processing towards more evaluative processing. Specifically, these areas are linked to the introspective evaluation of internal mental states, i.e. one's own thoughts and feelings, and might indicate self-referential processes in aesthetic evaluations. Kupchak et al. 2009. In another study, Kerr, Skoff, Hume, Christensen, and Zeki, 2009, showed that top-down classification of stimuli by defining them as genuine artworks, and hence framing an aesthetic context, or as computer-generated, changed evaluative stimulus processing. Participants gave higher aesthetic ratings for the same material presented as art as compared with non-art. Analyses of the brain states revealed that this was accompanied by specific changes in brain activations in the medial orbitofrontal cortex, which indicates hedonic value. Additionally, the prefrontal cortex was more strongly activated. The authors argue that this pattern of activation is consistent with subjects' expectations about the hedonic value of aesthetic experiences leading to an evaluative processing of the artwork. These studies also provided evidence for the prediction of enhanced stylistic and formal processing in aesthetic evaluations. For example, Kupchak and colleagues, 2009, reported that painting style influenced emotional ratings only in an aesthetic context. This 66 Helmut letter, Chernoff-Berger, and David Grieber was corroborated by a specific neuronal activation pattern. Perceptual visual areas associated with analyses of these structures, like the left superior parietal lobule, BA7, were more strongly activated in the aesthetic compared to pragmatic context. Additionally, Kerr, Skoff, Hume, and colleagues, 2009, reported increased activations in the primary visual cortex during aesthetic evaluations. Enhanced activation in these areas is attributable to a greater cognitive load placed on the visual system through systematic analyses of stylistic aspects and formal, i.e. visual narrative, aspects of the paintings. Moreover, the entorhinal cortex and the temporal pole, see also Jacobson et al. 2006, were activated more strongly. Such activations are linked with declarative memory processes, Kroll et al. 1997, and Kimura and Kubota 1995, and, according to the authors, they reflect recollection of contextually appropriate art-related and cultural information such as recalling the specific style of the painting. Noguchi and Miroda, 2013, studied the combined effects of two factors, a contextual manipulation, defining artworks, Renaissance sculptures of human bodies, as genuine or fake, and, unknown by the participants, a stylistic manipulation, visually altering the proportions of the sculptures resulting in likenesses of deformed bodies, while recording EEG. As in the study by Kerr, Skoff, Hume, and colleagues, 2009, participants provided higher aesthetic ratings for artworks defined as genuine compared to those defined as non-genuine. Additionally, participants showed marginally higher aesthetic ratings for the original compared to the altered versions. Both manipulations also produced significant differences in the ERPs. The P200 component showed a more positive going waveform for genuine as compared to non-genuine artworks, and for original as compared to altered artworks. This suggests that both kinds of manipulations were integrated and processed in the brain very rapidly, after between 200 milliseconds and 300 milliseconds. The authors also conducted source analyses of the EEG data, which permits estimation of the locations in the brain where this activity was generated. The parietal and medial prefrontal cortices were the sources of activation when a genuine versus fake context or when the original versus altered stimuli were compared. Additionally, for the stylistic comparison the occipital cortex was more strongly activated. These findings are consistent with the studies of Kupchak and colleagues, 2009, Jacobson and his team, 2006, and Kirk and co-workers, 2009. Together, these studies confirm that context plays an important role in aesthetic experiences. It changes processing to a more evaluative style comprising activation changes in a widespread network of lower and higher order cognitive and emotional areas. Nadal et al. 2008, Chaturji 2003, Vessel et al. 2012. It is a long-standing issue in the arts as to whether changes in emotional processing reflect genuine emotional reactions or whether these are specific to aesthetic experiences. Fryu 1988, Skur 2005. In the next section we will discuss how emotional experience is affected by aesthetic processing. 4.3.2 Where physiology plays the decisive role. Aesthetic emotions. Philosophers and psychologists have discussed whether emotions triggered by the arts are different from common everyday emotions. Beardsley 1958, Fryu 1988, Skur 2005. Skur sees a crucial difference between aesthetic and everyday emotions, which aesthetic appreciation 67 he calls utilitarian. Utilitarian emotions serve adaptive and homeostatic purposes to secure the well-being of an individual in significant events in life. Besides appraisals of novelty and intrinsic pleasantness, they comprise motivational appraisals like approach or withdrawal, action appraisals like fight or flight, and appraisals of coping potential, all designed to fulfill current and future needs. Aesthetic emotions, on the other hand, lack this kind of necessary immediacy of adapting to current events. They are instead produced by intrinsic appraisals of the aesthetic qualities of the object. Thus, motivational and action appraisals and the need to cope with the current situation should be less pronounced, or even absent, in aesthetic emotions. Skur 2005. Similarly, Freida, 1988, assumes that the intensity of emotional reactions is reduced when a person appraises an event as not realistic or not directly relevant to one's current or future needs. In aesthetic context, signaling a safe experience detached from reality, Beardsley 1958, provides the frame for such appraisals. For example, one rarely runs away from a cinema during a frightening horror movie, although fear-related responses will be triggered, including changes in facial expressions, increased heartbeat, and reported fear. Alternatively, some authors, Goldstein 2009, Martin Utley 2008, argue that because an aesthetic context lacks real-world consequences, it allows the individual to indulge in emotional reactions which are similar to or even stronger than those experienced in everyday life. Experiencing such emotions allows for risk-free practice for later life events. Desanayaki 2007, 2B and COSMX 2001, if and when similar circumstances require them. Only a few empirical studies tested whether and how aesthetic and everyday emotions differ, especially in the domain of visual art. Several studies employed a contextual manipulation, which is very similar to the distinction between aesthetic versus realistic processing, by telling participants that stimuli were either fictional, aesthetic processing has somehow a fictional character, 10-2000, or realistic. Goldstein, 2009, asked participants to watch films evoking sadness or anger under these two contexts and rated the intensity of their emotional experience. Additionally, participants rated the intensity of anger and sadness in personal events in real life. Overall, intensity ratings did not differ much. Participants reported equal amounts of anger and sadness when watching a film either in a realistic or fictional context. In relation to personal life events, participants reported more intense anger reactions but not more intense sadness reactions. This means that, at the very least, consciously reported intensity of emotional reactions is very similar under fictional and real life events. However, Mokaheiber and colleagues, 2010, 2011, reported that a fictional context attenuates components of the emotional reactions to negative stimuli as indicated by psychophysiological and behavioral parameters. A fictional, as compared to a realistic, context led to reduced amplitude of the LPP, Mokaheiber et al. 2010, which is indicative of reduced emotional processing. Also, specific changes in heart rate, a lower defensive bradycardia reaction were observed, Mokaheiber et al. 2011, and reaction time slowed down. These results imply that emotional reactions to negative stimuli are attenuated within a fictional context, as a stimulus might not be judged to be relevant for oneself. Fryu 1988. 68 Helmut Letter, Gernot Berger, and David Grieber critically. These studies used a very specific contextual manipulation by framing a fictional context, which is related to an aesthetic context, but is not the same. See discussion in section 4.3.1, and they did not use visual artworks. Conversely, in the study by Berger, Letter, and Creamer, 2014, participants evaluated positively and negatively balanced visual contemporary artworks and pictures from the International Effective Picture System, IAPS, Lang et al. 1999, under an aesthetic. These stimuli are artworks, or a realistic context. These stimuli are press photographs depicting real scenes. To track changes of subjects' experiences, positive reactions were measured by levels of liking, of joy, and recording of the musculus zygomaticus major activity, and negative reactions by measuring anger, disgust, shame, sorrow, sadness, fear ratings, and musculus corrugator supercilii activity. Similarly to Goldstein, 2009, they did not find any changes due to context for negative reactions, suggesting a very similar emotional experience for negative aspects. However, they found some changes for the positive reactions. Specifically, in the aesthetic compared to realistic context, negatively balanced artworks received higher liking and joy ratings, which was accompanied by a stronger reaction of the musculus zygomaticus major. For the more realistic-looking IAPS pictures, only the joy ratings were influenced. Emotionally negative pictures were perceived less negatively, in accordance with Machaber's results, but also emotionally positive IAPS pictures were perceived less positively. These results are consistent with the following conclusions. An aesthetic context enables a more positive perception of negatively balanced stimuli, especially when they are artworks. At the same time, the context does not erase negative reactions to emotionally negative stimuli. Thus, positive and negative aspects of the emotional experience are differentially affected by an aesthetic context. This is consistent with emotional models which posit that positive and negative aspects of emotional experiences are processed somewhat independently in different subsystems. K-Schiappo et al. 1997, Norris et al. 2010. The results also imply that it is important to consider both positive and negative aspects of the emotional experience in order to answer the question whether and how an aesthetic context changes our emotions. We have seen that an aesthetic context changes our experiences on a cognitive as well as emotional level. In the next section we take a closer look at the early stage of information processing, from behavioral and physiological studies. 4.3.3 Early processes, changes in perceptual areas as was shown in figure 4.1, at the beginning of each visual aesthetic experience is a stage of perceptual processing. All psychological theories of art emphasize these kinds of processes. Perception, however, comprises a fairly complex set of stages and processes and involves the transformation of sensory information into visual experiences which to some extent elicit aesthetic pleasure. Chaturji, 2003, summarized this as early and intermediate visual processing. Several studies have shown that aesthetic processing results in enhanced activities in the early and intermediate areas of visual processing. Fairhall and Ishai, 2008, compared the perception of representational, ambiguous, and abstract artworks with scrambled control aesthetic appreciation 69 stimuli. The former showed stronger activation of the inferior occipital gyrus and gyrus fusiformis, where object form is processed, and the dorsal occipital cortex, which processes spatial properties of visual objects. Additionally, Kupchak and colleagues, 2009, found indications for stronger visuospatial analyses in an aesthetic context compared to a pragmatic context, and Kerr and his team, 2009, reported stronger activations in early visual areas, primary visual cortex, under an aesthetic context, see section 4.3.1. Additionally, increased activations in these visual areas correlate with subjective aesthetic evaluations. Vartanian and Goel, 2004, employing abstract and representational paintings, showed that activation in the occipital gyrus, including the fusiform gyrus, linearly increased as a function of subjective preference ratings. Similarly, Bessel and colleagues, 2012, used abstract and representational paintings as well, and reported linear increases of activity in visual areas in the occipitotemporal cortex as a function of subjectively reported aesthetic value. However, activation patterns in these early and intermediate visual processing areas often show little overlap in different studies, e.g. Nadal et al. 2008. They depend critically on task demands, instructions, procedures, and stimulus materials used. For example, aesthetic processing of representational as compared to abstract artworks engages networks of object perception more strongly. Fairhall and Ishai 2008, Vartanian and Goel 2004. Overall, empirical studies provided some evidence that early and intermediate visual processing areas are consistently more strongly activated during aesthetic processing. This stronger activation might reflect a top-down enhancement due to attentional and/or emotional processes. Willumir and Driver 2007. Further research is required in order to clarify the exact nature of these processes. The stage of perceptual analyses, figure 4.1, considers the effects of a number of variables that influence a given image's aesthetic appeal. Among these variables are complexity, contrast, symmetry, order, and grouping. The combination of psychophysiological and behavioral methods can be fruitful in clarifying the contribution of such perceptual factors. For example, according to Berlin, 1971, visual complexity affects aesthetic responses through changes in arousal. However, attempts to test this prediction by using abstract patterns and psychophysiological measures of EDA failed to detect any effect of visual complexity on physiological arousal. Berlin and Lawrence 1964. Krupinski and Walker, 1988, manipulated complexity with different levels of symmetry. Their participants rated asymmetrical, single, and double-axis symmetrical patterns according to their hedonic value while SCR was recorded. In contrast to Berlin and colleagues, 1963, they found a linear increase in SCR and hedonic ratings with an increase in complexity. These diverging results regarding the relationship between visual complexity and physiological arousal during the aesthetic evaluation of abstract patterns resemble results concerning the effects of visual complexity on art appreciation. Nadal and colleagues, 2010, sought to resolve the ambiguity concerning the results of complexity and art appreciation ambiguous, because some studies found that simplicity was preferred. Nadal and colleagues, 2010, combined various methods. They employed a large set of abstract and representational artworks as well as non-artistic images which 70 Helmut Letter, Gernot Berger, and David Grieber were selected to represent 3 levels of complexity, high, medium, or low. When participants rated these stimuli for perceived beauty, there was no clear pattern of influences of complexity on aesthetics. Interestingly, Nadal and colleagues, 2010, classified their stimuli according to several dimensions that in the literature had been discussed as determinants of complexity, such as the number and variety of elements, an image's three-dimensionality, the general appeal of symmetry, etc. When they analyzed the effects according to these dimensions, none of them had a general effect on beauty. The authors concluded that the perceived complexity might have more or less individual causes in different dimensions and that these variations might conceal clear effects of complexity on appreciation of artworks. However, the nature of the processes that determine how complexity affects the perception of artworks still remains an interesting topic for future studies. In Letter and colleagues, 2004, approach, the specificity of art is not so much related to formal features such as complexity, but rather it is assigned to the distinction between content and style. 4.3.3.1 Representations, content and style, art specific. Cookinky, Kraft, Jacobs, and Letter, 2009, showed how physiology can inform the processes concerned with explicit content recognition. They tested the hypothesis that at the moment of insight when content of an artwork is recognized, changes in emotional responses can be observed. They looked at Cubist paintings, whose content takes the viewer time to recognize, Eckert and Van Weringen 1996. Pablo Picasso and Georges Braque developed a style which depicts the content and simultaneously overlaid or combined perspective views. This style slows recognition because the constituting elements cannot easily be assigned to one view. In some cases, recognition of the depicted object exceeds several seconds. In everyday life, however, object recognition is usually very fast and takes only fractions of a second. Cookinky and colleagues, 2009, measured pupillary responses and showed that the moment of content recognition was indeed accompanied by an emotional response, figure 4.1. Thus, at exactly the same time as an artwork subject was identified, participants showed a pupillary response that could be interpreted as an elicited emotion of pleasurable insight. Style is considered an important feature in the processing of art. Letter ETAL 2004. Regarding the processes underlying the recognition of style and content, Augustin, Letter, Hetzler, and Carbon, 2008, studied the time it takes for style and content to affect the perception of artworks by presenting images for very short times. Two artworks sometimes the same, sometimes different, in content, style, by the same or different artist had to be evaluated according to their perceived similarity. With a presentation time of 10 milliseconds, viewers could only distinguish matters of content. However, perceived similarity also was affected by painting style with 50 milliseconds. Thus, temporally, style follows content. In a later study, Augustin, DeFranchi, Fuchs, Carbon, and Hetzler, 2011, employed ERP to study the neural time course underlying the perception of content or style. Participants viewed pictures that systematically varied in style and content and had to perform a go/no-go dual-choice task. Results again supported the hypothesis that in the processing of art, style follows content. Style-related information aesthetic appreciation 71 was available later than content-related information as indicated by certain ERP components, lateralized readiness potential LRP, and N200. In the future, physiological measures will serve to improve our understanding of the aesthetic experiences as they are experienced over time, and as we become able to measure short-term effects and dynamic changes continuously. 4.3.3.2 Art expertise and knowledge. Experts are experts because they know more about a given subject than most individuals, and their knowledge is deeper. Knowledge about an artist's work and life, specific art styles and movements, and the process of artistic production aids stylistic and conceptual interpretation. Letter ETAL 2004. The increased ability to interpret art, in turn, facilitates understanding and art appreciation. Psychological research on art expertise mainly used two approaches. I. Studying the effect of art-specific information on lay people's art experience. Or, 2. Contrasting lay people and art experts, people with formal training in the arts or art professionals. Both approaches revealed how knowledge and art expertise affects processing on a cognitive, perceptual, and affective level. Art-specific knowledge provided by additional information shapes processing on a higher-order cognitive level such as finding meaning, resolving ambiguity, and developing understanding. Due to their lack of pre-existing knowledge, lay people are particularly suitable for projects which systematically manipulated art-specific knowledge. Several behavioral studies using this approach showed that additional information positively affects art appreciation and understanding. Letter ETAL 2006, Millis 2001, Russell 2003, Swami 2013. However, this depends on relative expertise level and art style. Especially with regard to abstract art, additional information helps lay people adopt style-focused processing, opens new perspectives for interpretation, and therefore increases their understanding of what they are viewing. Swami, 2013, emphasized that increased understanding mediates the positive effect of additional information on art appreciation. However, the impact of additional information on art appreciation also relies on the pre-existing, relative, level of expertise. For example, Bell, Letter, and Augustin, 2006, presented abstract artworks with or without stylistic information to participants differing in their relative level of art expertise. Participants with low art expertise showed an increased liking for abstract art when style-related information was given. Participants with high expertise, in contrast, showed a decrease in liking. This negative effect of information on the appreciation of art was presumably due to its interference with pre-existing knowledge of the experts. Only a few studies examined the effect of additional information on art appreciation by employing psychophysiological measures. Linger, Fischmeister, Letter, and Bauer, 2007, studied the effect of stylistic information on the evaluation of abstract and representational art. Understanding increased when stylistic information was provided. However, on a neuronal level, artworks presented with stylistic information compared to artworks without stylistic information evoked a weaker activation mainly in left frontal and parietal networks. This could indicate that art-specific information, by increasing knowledge and understanding, helps to process artworks more efficiently on a neuronal level. Hyde ETAL 72 Helmut Letter, Gernot Berger, and David Grieber 1988, Length ETAL 2007. Taken together, these studies show that specific information and knowledge significantly affect understanding of art and its appreciation. Choosing another approach to investigate the effect of knowledge on evaluation of art, Peng, Nadal, Muller, Paul, Rosenberg, and Klein, 2013, compared the neuronal response of lay people and art experts while evaluating art in a set of control stimuli. Consistent with the study by Linger and coworkers, 2007, Peng and colleagues found that knowledge leads to more efficient processing on a neuronal level. ERP amplitudes of the P3D and LPP, which are linked to knowledge retrieval, were reduced for art experts compared to lay people. Interestingly, in the study by Peng and colleagues, these expertise effects were not limited to artworks, they also extended to control stimuli, filtered artworks and simple color field stimuli. This suggests that art experts in general have a different style of visual processing. This is partly supported by a study by Long, Peng, Chen, Jin, and Yao, 2011. They showed that early perceptual processes like color processing differs between art experts, artists, and lay people on a neuronal level. First, MRI scans revealed structural differences between artists and lay people indicated by higher density of gray matter in brain areas involved in color processing, before, for artists. Secondly, during a color naming task, artists showed higher activity in before than lay people. This contradicts the neural efficiency hypothesis, in which we would expect a decreased activity for artists. These diverging results imply that the relation between expertise and efficient neural processing may be limited to specific tasks, brain regions, or subtypes of art expertise, but see Neubauer and Fink 2009. Nevertheless, a concurrent finding is that the level of art expertise affects visual processing on a neural level. On a behavioral level, experts and lay people differ in how they visually explore artworks. Kupchik and Laszlo, 1992, assume that art experts have learned to focus on stylistic and conceptual features whereas lay people adopt an object-oriented style of processing typical for everyday perception. Several eye-tracking studies support this hypothesis. Lay people directed their gaze more often to pictorial content, but art experts attended more to structural and compositional features. Nodini ETAL 2009, Vogt and Magnus in 2007. Art expertise also influences effective components of aesthetic experiences. According to Litter and colleagues, 2004, understanding and successful interpretation, both core factors of art expertise, are self-rewarding and effectively positive. In line with this, Kirk, Scott, Christensen, and Nygaard, 2009, showed that architecture experts exhibited higher activity in brain areas associated with reward processing, medial orbitofrontal cortex and subcallosal cingulate gyrus, compared to non-experts when they evaluated pictures of buildings. If a high level of art expertise generally increases positive affective experiences of artworks, then art experts compared to lay people should also feel more positive even when they look at negatively balanced art. Letter, Berger, Grieber, and Swartz, 2014, addressed this issue by measuring emotional responses when art experts and lay people looked at artworks and non-artworks, IPS pictures, with effectively positive and negative content. In general, positive stimuli led to a higher zygomaticus activation and negative stimuli to a higher corrugator activation, and positive stimuli were left more than negative ones. Aesthetic appreciation 73, but this effect was modulated by expertise. In line with the argumentation that expertise fosters a detached, Beardsley 1958, style of processing, experts exhibited attenuated emotional responses as indicated by less extreme corrugator supercilii activations and less extreme valence ratings. Additionally, there was a specific effect of letting experts like negative artworks more compared to lay people. Thus, experts' reduced emotional reactivity might have fostered the positive aesthetic evaluation of even emotionally negative art. In addition, art experts' aesthetic evaluations are less susceptible to biasing information. In an fMRI study by Kerr, Harvey, and Montague, 2011, participants evaluated artworks which were unobtrusively presented with either of two company logos. One of them was supposed to be from the company sponsoring the study, which paid $300 for participation. Lay people showed higher liking ratings for artworks which were presented with a sponsor logo. Art experts, in contrast, did not show this sponsorship effect. For both groups, activity in the ventromedial prefrontal cortex, VMPFC, increased with lighting, but lay people showed an even higher increase for sponsored artworks. Interestingly, for art experts, dorsolateral prefrontal cortex, DLPFC, activity correlated negatively with sponsorship effect and showed a stronger connectivity with VMPFC. Activity in the DLPFC has been associated with top-down executive control and emotion regulation, which could explain why the sponsor logo had no effect on art experts' aesthetic judgments. Hence, art experts were less susceptible to external biasing information and, thus, more independent in forming their aesthetic judgment. In sum, knowledge as a core feature of art expertise seems to facilitate independent aesthetic judgments and enables us to master viewing artworks more extensively on a higher order cognitive level. Moreover, art knowledge and frequent encounters with art not only improves our ability to understand and interpret art, but also changes how we process art on perceptual and affective levels. 4.4 Conclusion. In this chapter we have covered a set of research topics from empirical aesthetics to show how they can be studied by employing psychophysiological methods. This overview is selective rather than comprehensive. Nevertheless, regarding most components involved in art experience, the combination of behavioral and physiological measures is very fruitful. Where affective states are concerned, facial EMG apparently can be a good method to adopt, but in the future, fMRI may prove more productive when looking at the involvement of brain regions. Undoubtedly, EEG will remain a valuable tool in the future, particularly with regard to studying the sequence of processes. However, there are also important restrictions. Our selection of methods is incomplete and future developments are already apparent. Capella and colleagues, 2011, studied whole body movements and the shifting of body weight towards or away from an artwork. Moreover, peripheral measures like heart rate variability and electrodermal activity might play a role in uncovering the nature of arousal and activation during art perception. Finally, much is anticipated from more network-based analyses of Scan74 Helmut Leder, Gernot Berger, and David Krieger activity, and from combining genetic research and brain function to uncover individual differences, and the field of eye movement research could be a rich source of data, only briefly covered here. Empirical aesthetics was often restricted to laboratory studies with distinct limitations. Labs at UTS are not representative of the diverse experiences one has in a museum and they might miss essential features. Technical limitations, for example, in the resolution of artwork reproductions, or their size, can obstruct research. Moreover, there is still a huge bias towards reception. Production of artworks, although hard to imagine in the high arts as a topic for cognitive experimenters, will be a rich field of future research. Finally, the objects of our inquiries, the arts, are in constant development. Today, the acknowledgement of contemporary world art, Vogel 2013, challenges the traditional Eurocentric concepts of high art, and it requires flexible, self-critical, and globalized views that are often not compatible with what psychologists currently understand as art. 5.1 Gaze movements as a literary model in art history. Gaze movements have been an issue in the history of art long before they became a research topic in psychology. Early evidence dates back to the 6th century, when in 553 the Byzantine historian Procopius of Caesarea described how the interior space of the Hagia Sophia, Istanbul, overwhelms the beholder. Each detail attracts the eye and draws it on irresistibly to itself. So the vision constantly shifts suddenly, for the beholder is utterly unable to select which particular detail he should admire more than all the others. But even so, though they turn their attention to every side and look with contracted brows upon every detail, observers are still unable to understand the skillful craftsmanship. In the course of early modern times, reflections on gaze movements have significantly increased in writings about art, and they were repeatedly used to justify aesthetic qualities. In the 1460s, the Florentine architect and sculptor Filariti explains the superiority of the round arch over the Gothic pointed arch by referring to the eye movements it induces. It cannot be doubted that nothing which impedes the sight in any way is as beautiful as the one that leads the eye rather than restraining it. Such is the round arch. As you have noticed, your eye is not arrested in the least when you look at a half-circle arch. The pointed is not so, for the eye, or sight, pauses a little at the pointed part and does not run along as it does on the half-circle. Filariti 1972, pages 231, translation by the authors, Denis Diderot, the French philosopher who was also a founding father of art criticism, went significantly further. In 1767, comparing two altarpieces by the painters Gabriel François Doyen and Joseph Maridine, he drew an explicit link between the composition of paintings and the gaze of the beholder. For Diderot, composition is an instruction to the eye, a path which the gaze follows in a certain order. He describes Fiennes' painting, figure 5.1, as follows: such is the path followed in perusing this composition: religion, the angel, the saint, the women at his feet, the listeners in the background, and those in the left background, the two tall standing female figures, the elderly man leaning forward at their feet, and the two figures, one a man and the 80 Raphael Rosenberg and Christoph Klein, other a woman, seen from the back and placed squarely in the foreground, this path descending gently, and meandering. A line of liaison that clearly, crispy, and effortlessly links the composition's principal features. Diderot 1995, p29, for Diderot, Fiennes' painting is an example of a beautiful line of liaison, whereas he finds Doyen's piece, figure 5.2, very poor in this regard. In every composition there's a path, a line. If this line, which I call the line of liaison, bends, folds over onto itself, twists, is agitated, if its circumvolutions are diminutive, multiple, rectilinear, and angular, the composition will be ambiguous and obscure. The eye, wandering at random through a labyrinth, bewildered, will find it difficult to grasp the connections. If it is broken, the composition will have empty spots, holes. Doyen's miracle of St. Anthony's Fire is not above reproach in this respect. Its line of liaison is fractured, bent, folded, and twisted. It is difficult to follow. Sometimes it's ambiguous, or comes to a sudden halt, or requires considerable indulgence from the eye that's trying to follow its course. A well-ordered composition will always have but one true line of liaison, and it will serve as guide to anyone looking at it as well as to anyone attempting to describe it. Diderot 1995, p152, figure 5.1 Joseph Maridine, St. Dennis Preaching in Gaul, 1767. Copyright The Art Archive/Collection Dagli Lordi. The moving eye of the beholder 81 is an academic discipline. Art history was established in the middle of the 19th century. The language it used was based on much older writings about art. The idea of the movement of the eye is related to the aesthetic and the structure of the work of art was to remain an important paradigm of this new discipline. Some art historians thought that stylistic differences between artworks of different times and places were due to changes in the behavior of the eye. Thus in 1899, Heinrich Wölfflin, one of the most influential art historians in the early 20th century, explains the difference between the Italian arts of the early Renaissance, that is, the 15th century, and the high Renaissance of the early 16th century by the eye's need to relax. The Quattrocento placed unbelievable demands on the eye. The viewer not only has the greatest difficulty in picking out individual physiognomies from the serried ranks of heads, but the figures are only discernible in fragmentary form. By contrast, what great ocular satisfaction there is to be derived from the compositions of Raphael with the many figures. Wölfflin 1899, p292, translation by the authors, figure 5.2 Gabriel François Doyen, The Miracle of St. Anthony's Fire, 1767. Copyright The Miracle of St. Anthony's Fire, 1767, oil on canvas, Doyen, Gabriel François, 1726-1806, Église Saint Roch, Paris, France/Roger Violet, Paris/Bridgman Images. 82 Raphael Rosenberg and Christoph Klein in 1912, Wilhelm Weitzel, who later became Director General of the State Museums in Berlin until the Nazis removed him from his post, explained the differences between the Italian and the German/Dutch style in Renaissance art as having a basis in national differences in the eye's aptitudes. Italians have an architectural plastic talent accustoming the eye to trace the form of things, to see each individual figure in space and to ascertain the physicality of a thing by scanning it with the eye. The Italian vision isolates, the vision of Dutch people and Germans connects, the former is used to the mobility of gaze, the latter to the quiet looking eye. Way it sold 1912, P211FF. Translation by the authors. Perception remained a central topic in art history throughout the 20th century. On the one hand, the idea of the eye following the composition of artworks was sustained. On this basis, the art historian Kurt Vadt, 1961, for instance, developed a general method for the interpretation of paintings, insisting that the path of composition normally begins and should begin at the lower left-hand corner of pictures. Rosenberg 2014. On the other hand, a more general, though sometimes rather metaphorical discussion about cultures of perception, also addressed as scopic regimes, figured prominently not only in art history but also in visual culture studies, a new discipline which emerged from this very discussion in the 1990s. Foster 1988, Bolkinan 2011. In speculating about the eye movements of virtual beholders, art critics and art historians touched upon a field that would later evolve as a central method in psychology, the recording of gaze movements to investigate cognitive processes. Psychological advances were made possible by the description and by recordings of the saccadic nature of eye movements by ophthalmologists since the end of the 19th century. See section 5.2. But art historians did not take note of it for over 100 years. First discussions appeared in Frankenberg 1990, P144FF, Baxendal 1994, P413, Klossberg 1999, Rosenberg 2000, P49FF, Giuliani 2003, P27FF. In the following sections we will introduce the measurement of gaze movements as a prominent psychological technique and outline its neural basis in relationships with visual attention before reviewing what we have learned so far about eye movements of the beholders of paintings from experiments. 5.2 Analysis of gaze movements as a psychological method. 5.2.1 Overview. Gaze movements are basically alternations between periods of the eyes remaining relatively stationary, which we call fixations, and shorter periods of greater mobility, which we call saccades, from the French word saccade meaning jerk. Figure 5.3. This was described for the first time in 1879 by Jabal and Lamare, Jabal 1879. 2 decades later, Erdmann and Dodge reported the first successful attempt to record and measure eye movements empirically, Erdmann and Dodge 1898. Not only did this pioneering technological work lay the foundations for eye movement research in clinical populations, Klein and Ettinger 2008, but it also opened the field for experimental the moving eye of the beholder 83 psychological eye movement research, Wade and Tatler 2005. Nowadays, the study of gaze movements figures prominently in basic and applied psychological research. In basic research, gaze movement analyses have been used to study interactions between covert and overt attention processes, e.g. Henderson et al. 1989, Hoffman and Subramanian 1995, Reading, Henderson and Ferreira 1993, Problem-solving processes, Grant and Spivey 2003, Knoblich et al. 2009, Exploration of geometric patterns, Manor et al. 1995, Noten and Stark 1971c, The Study of Faces, Mertens et al. 1993, Film Watching, Smith 2014, Visual Processing of Media, Butcher and Schumacher 2012, The Analysis of Visual Scenes, Rayner et al. 2009, and in paintings. In applied research, gaze movements have been used to study, for example, product designs, Carbon et al. 2006, and print advertisements, Peters et al. 1999, to construct human-computer interfaces, Jacob and Karn 2003, to investigate processing of social situations in autistic patients, Klein et al. 2009, and problem-solving strategies in patients with Parkinson's disease, Hodgson et al. 1999, and first episode schizophrenics, Huddy et al. 2009. Figure 5.3 saccades, white arrows, and fixations, black circles, of the beholder whilst viewing Bean's painting, St. Denis Preaching in Gaul, 1767, 420s. Adapted version, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. 84 Raphael Rosenberg and Christoph Klein. 5.2.2 Measurement of gaze movements as a distinguished method in psychology. There are at least 3 reasons for the popularity of eye movement recordings in psychological research: importance, immediacy, and versatility. Gaze movements are important to investigate because the ocular motor system is doubtlessly the most used system among the sensory motor systems in primates, supported by an extensively distributed functional neural system that is currently better understood than any other functional system of the primate brain. Due to the anatomy of the eye, this system's effects can be investigated with an unmatched degree of immediacy, both psychologically and technically. As there is only one small spot of highest visual acuity on the retina, the fovea centralis, both the exploration of the visual world and our responses to its changes require our gaze to move as a series of fixations and saccades which, together, provide the best available model of the structure of human consciousness unfolding in space and time. The final virtue of eye movement studies is the versatility of their application in all kinds of basic as well as applied scientific settings from everyday situations, e.g. Hale and Bauer 2005, to the narrow setting of functional magnetic resonance imaging, fMRI, scanner and experimental paradigm. 5.2.3 Fixations and saccades. The analysis of gaze movements crucially hinges upon a. The definition of fixations and saccades, and b. The method of their grouping. We will explain the definitions in the following, and discuss methods of grouping in section 5.4. Regarding the definition of fixations, if we assume that there is a continuum between fixation, considered as periods of relatively stationary gaze that are characterized by the presence of microsaccades, or fixation saccades, plus drifts, and exploration, considered as periods of relative gaze mobility that are characterized by the presence of larger amplitude saccades, and drifts, Otero Millen et al. 2013, the definition of fixations in terms of degrees of displacement of the eye is, to some degree, arbitrary. Similarly ambiguous is the question as to what minimum duration a so-defined fixation should have, as this parameter is likely to be different for different kinds of tasks in different individuals. Accordingly, various definitions of fixations have been suggested in different domains of the literature, but these have been rarely compared empirically. See Manor and Gordon 2003. Typically, periods of relative gaze stationarity of at least 200 milliseconds are considered as fixations. However, this definition has been based on early reading studies and may thus be inappropriate for other visual tasks that use visual stimuli that are more complex or less complex than words. Extracting the gist of a complex scene, for instance, takes less time, 4100 ms, than analyzing it, with minimum fixation durations of 150 milliseconds. Rayner et al. 2009. Fixations during reading also take at least 140 milliseconds according to McConkie and colleagues, 1992, but Silici et al. 2003. Westheimer, 1954, but see Manor and Gordon 2003, reported intervals between successive saccades of 150 milliseconds. Similar values, ranging between 100 milliseconds and 200 milliseconds have been reported in later studies, Van Dypen et al. 1995, Harris et al. 1988, but see Manor and Gordon 2003. Rousseau and Rosen, 1975, used minimum fixation durations of 200 milliseconds to investigate gaze movement patterns during the moving eye of the beholder 85 reading and selection task. Even longer fixation durations, say, of 320 milliseconds for the analysis of geometric stimuli, Manor et al. 1995, have been reported as well. This latter figure corresponds well with the average fixation duration of about 320 milliseconds which we found for the participants of our study, irrespective of the painting they viewed, unpublished work. Fixation durations, however, not only differ between situations but also between individuals, and within individuals. Furthermore, speaking about the painting reduced fixation durations by about 40-50 ms, Klein et al. 2014. and interindividual fixation durations vary greatly between 200 milliseconds and 800 milliseconds, with a preference for 250-400 ms. Mertens et al. 1993. One of the few studies that empirically investigated the impact of different fixation definitions on gaze movement parameters was published by Manner and Gordon, 2003, who compared different fixation thresholds. Comparing 200 milliseconds and 100 milliseconds thresholds, this study reported significant increases in the number of fixations, total fixation duration, and scan path length, defined as a continuous line drawn through consecutive points of fixation, as well as significant decreases in average fixation duration for geometric and phase stimuli. Particularly noteworthy here is the association of the shorter fixation threshold with increased scan path lengths, underlining the perceptual cognitive significance of this relatively short, 100 milliseconds, fixation threshold. Also, schizophrenic patients could be more accurately discriminated on the basis of 100 milliseconds as opposed to 200 milliseconds fixation thresholds in showing less fixations in shorter skin paths, as well as longer overall fixation durations. Fixation parameters may differ according to stimulus types. Manner and Gordon, 2003, compared phase stimuli and geometric figures of the Ray-Oster-Reed complex figure type and found more numerous and shorter fixations for phase stimuli, independent of fixation threshold, 100 milliseconds or 200 milliseconds. Assuming again that fixation-related saccades and exploration-related saccades lie on a continuum and thus follow the same main sequence, Otero Millen et al. 2008, that is, the positive function relating the amplitude of saccades to their peak velocities, which holds for saccades 0.0350 degree in amplitude, Becker 1989, it is clear that the amplitude of saccades that are typically observed whilst participants are presented with various kinds of eye movement tasks on a computer screen are easily determined by their velocity curves and an arbitrary or calibration-based onset/offset criterion, e.g. 20 degrees per s or 20 per center of the amplitude of the velocity curve, Klein and Foster 2001. In such situations, saccades are easily recognizable as stepwise, discontinuous eye movements. It has been estimated that humans execute about 200,000 saccades per day, but see Fisher 1999. During these ballistic eye movements, the eyeball reaches peak velocities of more than 400 degrees per second. Fisher 1987, cf. Manner and Gordon 2003. Saccades are characterized by abrupt eye movement onsets with accelerations of up to 30,000 degrees/s2, peak velocities of 400-600 degrees/s, and an almost instantaneous termination of the movement. Becker 1989. While at least 7 different classes of saccades can be distinguished, see Becker 1989, refixation saccades, directed at objects that are selected beforehand from the environment, are of primary interest here. Such refixation saccades are frequently inaccurate and do not hit their target accurately. As a consequence, corrective eye movements, either glissades or corrective saccades, follow. The amplitude of the primary saccade may be too small, 86 Raphael Rosenberg and Christoph Klein, undershoot, or too large, overshoot. Undershoots prevail in the execution of large amplitude saccades, Fioravanti et al. 1995, and are followed by secondary corrective saccades as the second part of a pre-programmed two-step sequence, Becker and Fuchs 1969. 5.2.4 Physiological and neural basis of fixations in saccades. The visual system of primates has been investigated very intensively. Light enters the eye through the pupil and reaches two types of photoreceptors on the retina, rods processing dim light and cones processing bright light and colors. These photoreceptors accomplish a transduction that translates light information from a spotlight into an electric signal. The central fovea, a roughly 1.5 mm small area located about 5 degrees temporally to the visual axis, contains the highest density of cones and thus enables the most precise viewing. The axons of about 1 million ganglion cells leave the eye through the blind spot, form the optic disc, and transmit their neuronal information via the optic nerve, passing the optic chiasm and the optic tract to reach the lateral geniculate nucleus of the thalamus and from there the primary visual cortex, V1, and further the visual association cortices, V2, V5. From these association cortices the visual information spreads out to be processed by a complex system of cortical and subcortical areas. It is important to note that the central fovea covers only less than 1% of the retinal area but projects to a large portion of the visual cortex to process visual information coming from the central 2 degrees of the visual field. These mere anatomic conditions highlight two important functional aspects of the visual attention: its anatomically embodied selective nature and its close link with the continual alternation between fixations and saccades to reconstruct the visual outer world. The brain structures involved in fixations and saccades overlap to a large degree. This overlap can be expected by priori reasoning under the aforementioned assumption of a continuum between fixation-related and exploration-related saccades. These structures include A. The frontal eye fields, Bruce and Goldberg 1985, Bruce et al. 1985, B. The supplementary eye field, Vaughn and Lucchetti 1990, Schall 1991, C. Parts of the parietal cortex, Robinson et al. 1978, Anderson 1989, D. The substantia nigra of the basal ganglia, Kikosaka and Woods 1983, E. The superior colliculus, Doris and Munoz 1998, Schiller and Strecker 1972, and F. Regions in the brainstem, Hare and Gibbon 1994, Bruce 1990. While the functional system involved in gaze movements during the contemplation of visual art is already complex, it is by no means exhaustive with respect to the complexity of processes that are supposed, Letter et al. 2004, and can be experienced subjectively during the contemplation of paintings. 5.3 Visual attention and gaze movements. Functional, anatomic and neural features of the visual system outlined in section 5.2 not only underline the fact that the visual system is a system of information selection, they also indicate that visual attention unfolds in space and time as a continual alternation between fixations and saccades, or fixation-related and exploration-related saccades, which we will henceforth call gaze movements. Decades of experimental research with the moving eye of the beholder. 87 human and non-human primates have scrutinized these intricate relationships between visual attention and gaze movements, recently reviewed in Fowler 2011, in order to address among others two questions of fundamental importance: how do top-down and bottom-up factors interact, and what is the relative importance of low-level stimulus features, in particular, contrast, color, and motion, as opposed to higher-level stimulus structures, in particular, objects or gests. Einheiser et al. 2008. With regard to the importance of low-level features, Cook and Ullman, 1985, have suggested that locations within the visual field that exhibit relatively high physical salience are more likely to be attended and fixated. According to these authors, visual scenes contain spatial distributions of local contrasts of luminance, color, or movement that can be described in saliency maps and are processed in early stages of visual information processing. On the one hand, the concept of saliency maps is certainly theoretically intriguing and straightforward in predicting the locations of fixations better than models that posit random fixation locations. Powell, Sham and Underwood 2008. On the other hand, empirical research has shown that many further factors determine gaze positions and that these factors are more top-down than bottom-up. Such factors include strategic decisions to optimize task performance, such as looking at locations that maximize the probability of finding a search target, Najemnik and Geisler 2005, or looking near the center position of a scene to identify large portions of the scene with a single optimal viewing position, Tatler 2007. Another top-down factor is specific interests that direct the gaze to relevant areas of the visual field, e.g. looking at eyes and heads in social scenes to extract relevant social information, Birmingham et al. 2009. Similarly, interesting objects may attract the allocation of attention and fixations better than the perceptual saliency of an area of the visual field, Einheiser et al. 2008. Also, specific tasks can strongly impact which information participants select when looking at visual scenes. This includes the contemplation of paintings as well and will be discussed in the following section. Such bottom-up and top-down factors, rather than being mutually exclusive, are likely to interact. This was demonstrated, for instance, in Cerf and colleagues' 2008 study, which reported an improved prediction of gaze positions when the combined influences of top-down face preference and bottom-up low-level saliency were considered. These examples thus show that visual attention is controlled both by exogenous bottom-up processes of perceptual saliency and endogenous top-down processes. Chica et al. 2013. That visual attention unfolds in space and time suggests that it is the sequencing of saccades during the exploration of visual scenes, rather than an individual fixation or an individual saccade, that requires scientific investigation. In this regard, Cowler, 2011, has pointed to two principles that seem to rule the sequential selection of saccadic goals. According to the winner-takes-all principle, the area of the visual field that momentarily exhibits the highest strength, e.g. saliency, interest value, attracts visual attention. According to the inhibition of return principle, however, the selected area quickly, within a few hundred milliseconds, loses its strength to other areas to be fixated as the new winners. It is important to note that during such sequences of saccades to different fixation locations, the proper eye movements as manifestations of overt visual attention are ADA Raphael Rosenberg and Christoph Klein preceded by movements of covered visual attention to the location that is to be fixated next, Henderson et al. 1989. While the movements of covered and overt visual attention are temporally staggered, they are spatially isomorphic as it has been shown that it is impossible to orient attention, covertly, to one location while moving the eyes to another. Hoffman and Subramanian 1995. Gaze movements as the sequence of fixations and saccades to new locations generate skin paths across a stimulus of interest. Leach et al. 2003. Such skin paths were first described by Noten and Stark, 19718, 1971b, 1971c, who showed that when participants looked at visual patterns their gazes repeatedly created a fixed series of fixation locations, the skin path, that was characteristic for an individual participant. Noten and Stark also found that different skin paths were created by different individuals for the same pattern, and different skin paths by the same individual for different patterns. Interestingly, these skin paths remained consistent across different presentations of the same stimulus to the same participant and were even replicated when a previously scanned stimulus was removed and had to be imagined. The apparent existence of an ocular motor memory of an individual stimulus certainly stands as among the most compelling evidence of top-down factors in gaze movements. Gaze movements as alternations of fixations and saccades seem to be governed by two different states of visual attention, according to Leach and colleagues, 2003. During states of local visual attention and under the presumed control of the inferior temporal cortex, information is extracted from specific and proximal locations by means of short saccades. Conversely, during states of global visual attention presumably influenced by the posterior parietal cortex, long saccades are employed to integrate information from distal locations. According to Leach and colleagues, 2003, the interaction between temporal/local and parietal/global states is controlled by the prefrontal cortex. To summarize, the fact that only a very small area of the retina provides the best visual acuity requires visual attention to unfold as gaze movements. The dynamics of gaze movements are determined by perceptual bottom-up factors as well as cognitive or motivational top-down influences, governed by principles that regulate how a fixation location is selected and then abandoned as a new location is chosen, and may switch between local and global states of visual attention. 5.4 Gaze movements during the beholding of paintings. 5.4.1 History of research. What do we do when we behold works of visual arts? Given the central role of the ocular system in this process and in the light of the emphasis of gaze movements in literature on art, Section 5.1, eye tracking is logically among the foremost methods used to investigate this field. However, although the first comprehensive research dates back to the 1930s, the number of investigations into this area has remained rather limited. The psychologist Guy T. Buswell, 1891-1994, accomplished the first in-depth studies on how people look at paintings and published the only book to date about eye tracking and the moving eye of the beholder. 89 Art Perception, Buswell 1935. He recorded gaze movements of children and adults, of art experts and lay persons, of American and Oriental subjects looking at reproductions of works of art, paintings, drawings, prints, sculptures, buildings, applied arts, various in cultural origin, color, design, and balance, and the amount of detail incorporated. He included silhouettes and pictures with outline drawings as well as partly unfinished paintings. Compared to present-day eye trackers, Buswell's device was cumbersome for the experimental subjects and the data it provided were extremely time-consuming to analyze. However, he did manage to collect a total of 1,877 records from 200 different individuals looking at different pictures for several tens of seconds at a rate of 30 measurements per second. Buswell thoroughly addressed most of the questions that research in this area ever since investigated. His main chapters, the duration of fixation pauses, variations in perception related to characteristics of the picture, variations in perception related to characteristics of individuals, and variations in perception due to directions for looking at pictures follow a systematic order that we have adopted for the headings of the present section. Buswell and his collaborators at the University of Chicago were technically innovative, thoughtful in the design of their studies, and very rigorous in their methodologies. However, their overall conclusions are rather sobering. A contemporary reviewer noticed in the Burlington magazine, our admiration for the ingenuity of Professor Buswell's apparatus and the heroic laboriousness of his experiments and calculations may be a little tempered by our disappointment at noticing that nothing of the slightest importance to the sciences of aesthetics or psychology seems to result from this research. Dallas 1936, p. 58. In retrospect, one may say that Buswell's rather flawed general results were due to technical limitations. Buswell, 1935, p. 90, would have loved to investigate longer periods of beholding, especially with experts, but for technical reasons this was not feasible. In addition, without electronic data processing, his capacity for a comparative analysis of the huge amount of recordings was very restricted. Longer measurements of gaze movements when viewing images were first carried out by the Russian psychologist Alfred L. Urbus, 1914-1986. Some of the stimuli used by Urbus were works of art. However, the topic of his seminal book was eye movements and vision in a broader sense. He did not focus solely on art as Buswell did. Due to the very nature of art, the essence of which withstands any bold attempts at manipulation without being destroyed, and to the difficulty of offering aesthetic experiences in the cool atmosphere of a laboratory, scant proper experimental research has been accomplished regarding viewing visual art. Approaches that do not manipulate the painting to be viewed and which measure paintings in their original contexts are the most appropriate, but most studies were governed by the technical feasibility of eye trackers. Only a few studies have as yet been conducted in museums rather than in labs, and the limitations imposed on the subjects by wearing eye trackers are not negligible. Heidenreich in Toronto 2011, Capella and Instacart 2006. Worth bearing in mind too is that the time taken to look at artworks used to be quite short. The average time taken in most experimental settings was less than the mean time of 27.2 and median of 17.0 seconds, a period which general visitors were found to spend looking at paintings at the Metropolitan 90 Raphael Rosenberg and Christoph Klein Museum, Smith and Smith 2001, and was much less than the time art experts would consider sufficient to have an aesthetic experience. Massaro and colleagues, 2012, is a recent example using a viewing time of 3s. We assume that it can take several minutes to enjoy a work of art fully and to experience the aesthetic values of a painting that one does not know. The viewing time of experts such as artists or art historians, especially when speaking in groups with each other, can often last for several minutes, sometimes more than an hour, including alternating phases of silent contemplation and discussions about the artwork under consideration. In an interdisciplinary project between departments of art history and psychology, we sought to overcome these limitations as far as technically possible. In a first study at the University of Heidelberg, we recorded the gaze movements of 99 participants who were presented 4 facsimiles of paintings, looking at each for 15 minutes. The paintings had been reproduced in, almost, original size with the best photographic techniques currently available, were mounted with appropriate frames, and hung on the wall of an otherwise neutral room that, in terms of art exhibitions, would be defined as a white cube. We used a head-mounted eye tracker with an electromagnetic positioning system, SME-registered trademark iViews Head HT, that allows the participant to move within a radius of about 120 centimeters. Klein ETAL 2014. In a later series of recordings at the University of Vienna, subjects looked at high-quality digital reproductions of paintings on a high-resolution screen. Apple registered trademark 32,560 x 1,600 pixel, at a distance of about 90 centimeters, each for 2 minutes. Their gaze movements were recorded without any physical contact between subjects and the device. Remote eye tracker SME-registered trademark iViews RID 120. From the binocular recordings we processed the data recorded of the dominant eye of every subject. Brinkman ETAL 2014. 5.4.2 Variations of gaze movements during the time-lapse of beholding eye tracking enables a precise description of the time-lapse during the viewing of paintings, and this was always a central issue in eye tracking studies about art. One of the chief findings of Buswell, 1935, was that the duration of fixations tends to increase during the course of viewing. He differentiates two general patterns of perception within the first 10-15 seconds. The first phase of general survey with shorter fixations followed by a phase of more detailed study with longer fixation durations and, shorter, saccades concentrated over small areas of the picture. The major distinction between these patterns of perception has been confirmed and elaborated several times, among others by Berlin, 1971, Entis, 1974, and more recently by Liechti and colleagues, 2003, see section 5.3, Locker, 2006, and Locker and colleagues, 2007, in the light of cognitive theories. Molnar, 1981, accepted this distinction as well but tried to also distinguish a third kind of exploration with distinct patterns of the duration of fixations and of the length of saccades. He thought that these patterns also depend on the complexity and style of the painting, but he failed to give sufficient experimental evidence for his supposition. Our own studies, which for the first time consider much longer periods of time, endorse Buswell's findings and underline that there is a significant inter-individual variability in the duration of fixations, in the length of saccades, and in the sequence of different patterns of perception. The moving eye of the beholder 91 significant average changes to the duration of fixations and the length of saccades occur in the first seconds of viewing. However, repeated alternations of patterns of perception, oscillating between general survey and detail study continue for at least 15 minutes. Within the first few seconds, the average duration of fixation significantly increases. In the following minutes the slope of the curve becomes rather flat but the increase in duration of fixations endures. We interpret this as indicating a deeper perception that can be arguably related to aesthetic experience. This would confirm a study by Molnar and Rathikis, 1987, where a group of beholders that were asked to judge the aesthetic qualities of the picture had clearly longer fixations than another group of beholders who were simply asked to describe what they saw. 5.4.3 Variations of gaze movements related to paintings. Buswell, 1935, demonstrated that gaze movements meet common assumptions made in art literature, such as those reported in section 5.1, only in some respects. His numerous eye tracking graphs make clear that the eye hardly ever moves systematically along a composition line from one end to the other. Nevertheless, Buswell's work provided important indications as to the relationships between gaze movements and pictures. He showed that every picture has specific centers of interest that attract a higher density of fixations than other areas. Buswell 1935, pages 1824. Regarding gaze movements, his results were very restricted and his analyses limited to the two initial saccades into 3 images showing mainly vertical lines, interior of Gothic church, mainly horizontal lines, library of the Oriental Institute of the University of Chicago, and lines following the direction of a wave, focus eye, the wave. He states that his results were quite in accord with the general assumption that the eye will follow the direction of the principal lines in a picture. Buswell 1935, pages 79 and 82. Your Bus, 1967, pages 170-196, published single recordings of subjects viewing reproductions of landscape paintings for up to 30 minutes. Probably due to technical reasons, those visualizations only show a portion of the total fixations and saccades. However, they are revealing since they make clear that while beholding the same painting for many minutes the subject's eyes repeat the same movements. Your Bus talks about individually specific cyclical patterns. Molnar, 1981, 1992, came to similar conclusions, and described these visualizations using statistical methods as follows. The transition probability between the areas of interest of two paintings, by Titian and Manet, reached a stable state after just 20 or 25 saccades. Like the skin path described by Newton and Stark, 1971A, 1971B, 1971C, and C section 5.3, but see Manan ETAL 1997, Krieger ETAL 2000, those findings were related to single spectators. In our studies, Rosenberg ETAL 2008, Engelbrecht ETAL 2010, Brinkman ETAL 2014, Klein ETAL 2014, Rosenberg 2014, we have meanwhile shown 57 paintings from different epochs, 15th to the 20th centuries, in different genres, history paintings, portraits, landscapes, still life, abstract art. The viewing time was either 2 or 15 minutes and the number of participants varied between 10 and 99. Taken together, our studies confirm Buswell's conclusion that most paintings have specific centers of interest with significantly higher densities of fixations. Figure 5.4. This is hardly the case for paintings such as 92 Raphael Rosenberg and Christoph Klein Jackson Pollock's groupings. Figure 5.5, however, where the artist intentionally avoided a hierarchical composition and denied as much as possible any distinction between figure and ground, resulting in no single zone with enough fixations to be read in the heat map. For a significant number of paintings and despite major differences between subjects, not only fixations but also saccades build patterns that are specific to each painting, beholders tend to reiterate particular paths with their eyes. This is evident when the saccades of different viewers are superimposed. See figure 5.6 and 5.6b, with a reduction to 10% of all saccades to reduce confusion. Hence we conclude that the cyclical patterns observed by Your Bus, 1967, do not only occur for single subjects but are very similar for different subjects viewing the same painting as long as they do so for longer stretches of time. We have developed different methods to determine whether and how saccades repeat specific paths. Frequent cluster transitions show the spots, clusters, with the highest density of fixations and the often repeated saccadic transitions. We thereby define clusters of fixations as circular regions of a given diameter, here 90 pixels, containing more than a certain amount of fixations as per minute rate. For an alternative definition of fixation clusters see also Santella and DiCarlo 2004. An algorithm calculates the figure 5.4 heat maps of fixations of 40 viewers, 20 art experts and 20 non-experts, looking at Beans, A, St. Denis Preaching in Gaul, 1767, and Doyens, B, The Miracle of St. Anthony's Fire, 1767, paintings for 2 minutes each. Adapted versions Copyright Laboratory for Cognitive Research in Art History, University of Vienna. A, B, The Moving Eye of the Beholder 93 figure 5.5, A, Jackson Pollock's Convergence, 1952, and B, Heat map of fixations of 40 viewers, 20 art experts and 20 non-experts, viewing this painting for 2 minutes each. Albright Knox Art Gallery / Art Resource, New York / Stala, Florence. Copyright the Paul Krasner Foundation Ars, New York, and DACS, London 2015. Part B. Copyright Laboratory for Cognitive Research in Art History, University of Vienna. A. B. Amount of saccadic transitions between the fixations of those clusters. In figure 5.7 and 5.7b we visualize all transitions repeated at least 0.5 times per minute. The width of the lines between the clusters encodes the frequency of saccades, with more frequent transitions resulting in greater width. Color can be used to encode the direction of saccades. 94 Raphael Rosenberg and Christoph Klein, A, B, figure 5.610, per center of all saccades of 40 viewers, 20 art experts and 20 non-experts, beholding Beans, A, and Doyens, B, paintings for 2 minutes each. Adapted versions, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. The visualizations of gaze movements, see figures 5.3, 5.6 and 5.6d, show that Diderot's analyses, section 5.1, as well as similar claims recurring in the art historical literature do not match the real dynamic of the eye. The gaze jumps from fixation to fixation, moving forth in bed. Eyes do not follow any line of composition in a continuous manner, nor do beholders scan paintings from top to bottom or left to right continuously. In addition, the general assumption of art historians, BADT 1961, Wolflin 1941, that viewers' eyes predominantly move from left to right as when reading when looking at European paintings is empirically incorrect, since the average direction of saccades between most clusters of fixations tends to be balanced in all the paintings we have studied to date. However, the analysis of average eye movements, both for fixations, figure 5.4 and 5.4b, and saccades, figure 5.7 and 5.7b, reveals that several aspects of Diderot's text are indeed correct. Viewers concentrate much longer on certain parts of Bean's painting, greater amount of red areas in the heat map, whereas their fixations are more scattered when looking at Doyen's piece. This corresponds with Diderot's description of the differences between those altarpieces. His description of a line of composition in Bean's altarpiece is correct as long as we consider the frequently repeated saccades and not the actual the moving eye of the beholder 95 course of the movement of the eye. The line he describes matches the graph of the most frequent saccadic transitions between clusters of fixations, figure 5.7a. Correspondingly, it is clear that the saccadic movements executed when viewing Doyen's painting, figure 5.7b, connect the figures within the four groups, but they do not connect those groups with each other quite as much. In contrast, fixations are almost equally distributed when looking at Pollock's canvas, figure 5.4, and this corresponds to the all-over, a term commonly used to describe his canvases covered with paint from edge to edge, without preferences. Another method to illustrate and evaluate the paths repeated by the beholder's eyes is the visualization of similar saccades. We developed an algorithm merging all saccades that are more or less close to each other and run more or less in parallel to each other. This method is useful for paintings that do not have clear centers of interest like human figures and especially faces, for example, landscapes, abstract images, etc. Figure 5.8 and 5.8b. We have chosen the altarpieces by Bean and Doyen because Diderot's description of hypothetical eye movements during the contemplation of these paintings is prominent in the history of art literature. However, those altarpieces stand for a wide range of paintings where the fixations and saccades of almost all beholders repeat. Figure 5.7 frequent saccadic transitions between fixations clusters for Bean's A and Doyen's B paintings, average of 40 viewers, 20 art experts and 20 non-experts, whilst viewing for 2 minutes each. Adapted versions, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. A, B, figure 5.820, per center of all saccades and visualization of similar saccades of 20 viewers, 10 art experts and 10 non-experts, whilst looking at CD. Friedrich, de Watzmann, 1824/25, for 2 minutes each. Copyright at images. Adapted versions, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. The moving eye of the beholder 97 patterns that are specific to the composition of each painting. Those patterns often match the analysis of the paintings given by art critics over the centuries, and they are very similar to diagrams of composition of those paintings, as they have been sketched by artists and art historians since the second half of the 18th century, Rosenberg 2008. We thus conclude that the eyes of beholders do indeed often reconstruct the structure of paintings, and that the repetitions of the structures of works of art with our eyes might be a basis for aesthetic experience. As with Diderot's text, subjective analysis seems often a kind of general summary of real-life gaze movements, an abstraction of factual gaze movements highly influenced by cognitive processes, such as the awareness about the content, iconography, of the painting. Knowledge about the content and the history represented in a painting affects the order in which we arrange the pieces of this painting in our minds and hence the order in which we describe it, regardless of the fact that our eyes perceive these parts again and again in alternating sequences. However, for some types of paintings the patterns of gaze movements do not mirror their structure. This is particularly the case for paintings where faces are dominant, as in portraits, since the beholder's eyes mainly concentrate on eyes, nose, and mouth, and very few other details. Figure 5.9, although any art critic and most art viewers will normally describe many more aspects of the painting than those facial details. Another limitation is given by the fact that gaze patterns only appear if the painting has points of reference, saliencies in regard to form and or content. This is less the case for abstract than for figure 5.9 frequent saccadic transitions between fixation clusters of 40 viewers, 20 art experts and 20 non-experts, of Vincent van Gogh, Portrait of a Peasant, 1889, whilst beholding for 2 minutes each. Copyright Portrait of a Peasant, Go, Vincent van, 1853-1890, National Gallery of Modern Art, GNAM, Rome, Italy. Copyright Photoscala, Florence, courtesy of the Ministero Beneatt, Culturali. Adapted version, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. 98 Raphael Rosenberg and Christoph Klein Representational Art, Brinkmann ETAL 2014, and of course even less for color field or even monochrome paintings where fixations and saccades do not form any patterns. 5.4.4 Variations of gaze movements related to beholders. There is literally no psychologically relevant feature in which individuals do not differ greatly. Given the complexity and general openness of art to varying interpretations, Echo 1962, individual differences can be assumed to be particularly relevant with regard to the way people look at paintings. Indeed, pronounced individual differences in gaze movement patterns while looking at paintings had already been noticed by Buswell, 1935. 3 decades later, Yarbus, 1967, p. 192, concluded that individual observers differ in the way they think and, therefore, differ also to some extent in the way they look at things. Locker, 1996, analyzed individual subjects' fixation distributions and reported individual differences in identifying the visual center of a picture, an individual's mean eye position. In one of our studies, Klein et al. 2014, given its large sample size and long recording duration, we also looked at various eye movement parameters, grouped according to factor analysis into saccades, fixations, and transitions between fixation clusters. We found individual differences in all of these factors to be highly stable across the viewing time of 10 minutes. Unpublished work. These individual differences were, furthermore, somewhat consistent across the 4 paintings of this study. Overall, our results thus suggest that individual differences in elementary facets of gaze movement control during the contemplation of paintings are stable across stretches of several minutes and are consistent across different types of painting. Hence, we can assume major personality-related contributions, the nature of which is yet to be determined, to the way people look at paintings. Beyond inter-individual variances, group-specific differences are one of the most interesting topics of eye-tracking research about the perception of images both for psychology and art history. Buswell, 1935, asked about differences due to expertise and culture but he was not able to discern any. Chris Jansen and Entes, 1989, reported differences in gaze movement patterns between artists and non-artists that seemed to correlate with the familiarity of the paintings. Artists showed longer fixations during the contemplation of known paintings and shorter ones with unknown paintings, whilst the opposite held for non-artists. The importance of art expertise for the way people look at paintings has also been emphasized by Nodini and colleagues, 1993. They presented original and manipulated paintings for 12 seconds to artists and non-artists and found that untrained viewers failed to recognize the perceptual organizing function of pictorial elements. Furthermore, Zangmeister and colleagues, 1995, compared the gaze movements of art experts and laypersons when viewing representational or abstract paintings. While fixation durations did not differentiate paintings or participant groups, art experts were found to explore paintings with longer saccades than non-experts. This group difference was more pronounced for abstract as compared to representational paintings. Vogt and Magnuson, 2007, as well as Steele and colleagues, 2011, also described differences in viewing strategies influenced by expertise. The moving eye of the beholder 99 in our studies. For the first time we compared experts, students of art history above degree level, and non-experts, students from the same university not interested in art, for viewing periods longer than 1 minute per painting. We did not detect any differences between the two groups for non-complex paintings. By contrast, we found that for complex paintings these groups differed in their eye movement patterns, but only at the beginning of the contemplation for periods of time of several tens of seconds. Rosenberg 2014. In the case of Wien's altarpiece, for instance, such group differences lasted for approximately 30 seconds. Figure 5.10. One possible explanation is that non-experts might need more time to understand the structure, the intrinsic meaning of the painting. Conversely, experts are faster in mapping the structure of a painting, in particular when it is complex. Given the fact that historical changes can be described as cultural changes, a crucial question for art historians is whether and to what extent the cultural imprint may influence looking at artworks. Art historians have discussed whether stylistic changes in art might be due to changes of cognitive modes, Baxendale 1972, and whether the perception of artworks has changed during centuries, Rosenberg 2000. We are currently carrying out a project on the cultural eye, by doctoral student Anna Brinkman, focusing on A, B, figure 5.10 frequent saccadic transitions between fixations clusters of 20 art experts, A, and 20 non-experts, B, whilst looking at Wien's painting for 30 s each. Adapted versions, Copyright Laboratory for Cognitive Research in Art History, University of Vienna. 100 Raphael Rosenberg and Christoph Klein. Differences between Japanese and Austrian beholders. In a preliminary study with 6 Japanese and 6 Austrian test people looking at 10 paintings for 2 minutes each, we found significant differences. The Japanese concentrated on the background of the paintings, compared Poland ETAL 2008, Nisbet ETAL 2001, Nisbet 2003, and made fewer horizontal and more vertical saccades, compared to the Austrian individuals, figure 5.10. This might be due to reading habits. Finally, the Japanese executed longer fixations. This could be due to the fact that all paintings in this test were European, hence might have been unfamiliar to the Japanese viewers. 5.4.5 Variations of gaze movements related to task and context. Buswell, 1935, pages 136, 41, 144, demonstrated that the directions given prior to looking at pictures have a marked influence upon the character of perception. Yarbus recorded the eye movements of a beholder viewing the reproduction of a painting by Irupin, with 7 different instructions such as give the ages of the people, or remember the position of the people and objects in the room. The page illustrating those recordings, Yarbus 1967, P174, has been quoted regularly, and the experiment was replicated with 17 observers, DeAngelis and Pels 2009. There can be no doubt that the variation of task has a stronger influence on gaze movements than differences between beholders, and it is interesting to use paintings to test such differences and hence demonstrate the top-down control of gaze movements. However, instructions as used in the Yarbus experiment are alien to the purpose of paintings as works of art and to the normal conditions of their beholding. More relevant to the understanding of aesthetic processes is an experiment conducted by Molnar and Radzikas, 1987. They compared gaze movements of participants looking at 15, 11, 17, 16, 19, 12, 10, 10, 17, 12, 11, 11, 8, 12, 10, 8, A, B, figure 5.11 average direction of saccades, percentage, of 6 Japanese, A, versus 6 Austrians, B, non-experts test individuals looking at CD. Friedrich, de Wattsman, see figure 5.8, for 2 minutes each, 8 segments of 45 degrees, arrows are segment bisectors. Copyright Laboratory for Cognitive Research in Art History, University of Vienna. The moving eye of the beholder. 101 reproductions of paintings knowing that they were expected to report verbally later on either the semantic content of the paintings or their aesthetic qualities. The group with the aesthetic instruction had significantly longer fixations. Until the 18th century, paintings normally did not have titles. Yet, in the course of the 19th century, titles became an integral part of works of visual art. Viewers nowadays often look at a painting after they have read its title. The title might hence be regarded as an element which guides the eye of the spectator, and artists and art historians are thus aware of the importance of titles for the spectator. Welchman 1997. Capella and colleagues, 2009, demonstrated that at least in the case of Fernand Léger's Cubist paintings, which include rather unclear motifs, knowledge of different titles has a significant influence on gaze movements. The normal task for the spectator of art is to speak about the observed works. Since the Italian Renaissance, talking about artworks in front of them was a common practice not only among artists but also among the growing group of interested laypersons, connoisseurs and, later, art historians. There are extensive sources on discourses and descriptions of paintings that were originally spoken in front of the works of art, Welto 1997, and the practice of describing works of art remains fundamental in museums and art history courses. In order to understand whether and how speaking about the work influences the processing of beholding, we designed a study in which participants contemplated paintings, selected to cover different genres, for 10 minutes, followed either by a period of up to 5 minutes during which participants were required to answer several open questions regarding the painting or by a period of 5 minutes of continued silent viewing. The results suggest how striking an effect speaking has on the way people look at paintings, consistent with a shift towards the global state of attention, that is, not focusing on details. See section 5.3. Participants employed shorter fixations and longer saccades while they were speaking compared to silent beholding. In addition, the number of transitions between clusters of fixation significantly increased. We therefore suggest that speaking about known visual artworks activates a mnemonic representation of a particular painting, built up during the previous period of viewing that guides gaze movement control during a global state of attention and in partial disregard as to the details. Klein ETAL 2014. We also assume that context affects the reception of art in general and gaze movements of spectators in particular. As long as eye trackers could be used only in laboratories, it was not possible to test contextual influences. Thanks to new devices which enable eye tracking of mobile spectators, some studies have begun to investigate the influence of the context where paintings are exhibited. Reber ETAL 2014. 5.5 Conclusion and directions for future research. The mutual interest between art history and psychology can be traced back through over a century of research. Fechner, 1876, one of the founding fathers of psychology, was also a pioneer of experimental investigation of aesthetics just as Wolflin, 1886, 102 Raphael Rosenberg and Christoph Klein and Riegel, 1901, two leading figures in art history during their own lives, developed psychological approaches in order to gain a basic understanding of the historical evolution of art. Since the 1950s, publications of the psychologist Rudolf Arnheim were read by artists and art historians, as those by the art historian Ernst Gombrich were by psychologists. In terms of major recent developments in psychophysiology, eye tracking is probably the most promising technique, opening new horizons for collaborative research on the psychology of visual arts. The scope of this collaborative research is as broad and versatile as the many disciplines involved. It requires decisions about what should be some fundamental questions, and it offers the possibility of addressing a range of relevant topics. Among the fundamental questions are the following. First, what is the nature of the setting in which the appreciation of art is to be studied? While the vast majority of the limited number of studies in the psychology of visual arts have been conducted in the laboratory, ambulatory assessment nowadays uses versatile equipment which can be used to study the viewing and appreciation of art in environments that are more valid than the laboratory, such as museum, gallery, or the home. These studies would not be confined to subjective reports, e.g. using mobile devices which could be used to prompt responses, such as cell phones, or the measurement of gaze movements. They could investigate a wealth of psychophysiological processes supposedly associated with the appreciation of art, e.g. pupil diameter, electroencephalography, heart rate, skin conductance response. Here, as in all domains of ambulatory assessment, the gain in ecological validity comes at the expense of soft and cause-effect relationships, internal validity, which still can be ascertained best in the laboratory. Secondly, what kind of CO variation should be investigated? Should it be natural CO variation such as the variation of aesthetic judgments across the paintings exhibited in a gallery, or experimental CO variation such as the changes in brain responses to a painting as a consequence of varying beholding instructions? Here, the fundamental question is whether to vary or manipulate the painting or the beholder, or both. Varying paintings, for example, by comparing abstract versus representational paintings or by comparing paintings from different epochs leaves the object of study intact but renders the analysis of its effects ambiguous due to the many differences between paintings. Conversely, manipulating paintings, for example, by applying graphical filters to alter colors, contours, and the like, or relocating its elements to alter symmetry or composition may yield at best clear cause and effect relationships, but possibly ones that border on art historical irrelevance due to the artificial nature of the manipulation. Varying, by selection, or manipulating, by instruction, the beholder, by contrast, tells us little about how a piece of art influences our perception of it. This individual-centered approach instead emphasizes the subject of the process of constructing beauty in the eye of the beholder and offers a variety of different approaches such as the following. We can study the impact of individual-related variables such as the degree of art expertise, age, gender, and cultural background, cross-cultural and subcultural, as well as their interaction by keeping the object artwork constant. This approach can be easily combined both with the art-centered approaches outlined earlier, the moving eye of the beholder 103, and with individual-centered manipulations of viewing instructions. Such instructions can focus on aspects of the paintings, e.g. its colorfulness, contents, etc., or the processes in the beholder, e.g. remembering, evaluating, etc., or both. All these approaches have been employed in the pertinent literature so far, albeit often not in combination with the recording of gaze movements. Due their close coupling with visual attention, detailed in section 5.3, gaze movements should be more systematically recorded in these endeavors. Irrespective of the selection of approaches chosen, there are a number of topics that should be addressed in future research of the psychology of visual art. First, given the importance of hypothetical eye movements for the analysis of visual art, see section 5.1. More empirical work using gaze movement recordings is required to revise and possibly to reevaluate and extend this kind of theorizing on the basis of firm empirical data. Secondly, given the inherently subjective nature of aesthetic experience and the openness of any kind of art, the systematic study of personality, in the broadest sense of the term, factors in looking at artworks is of utmost importance for this field of research. This does not only refer to the influences of gender, age, expertise, general education, general intelligence, or culture, with its pertinence for historical studies, see section 5.4.4, but it also touches upon the influences of situational factors, gallery versus lab, or the stability of individual differences. Thirdly, the observed gaze movement pattern should be validated against psychologically meaningful parameters, e.g. does fixation duration predict encoding success? Is the understanding of an artwork's complexity related to the complexity of the gaze movement patterns? Fourthly, assuming that art is essential to the education systems of many cultures, how can we utilize the measurement of gaze movements during art contemplation to foster the understanding of art at different ages across the lifespan? Furthermore, eye tracking studies have been used already in the field of conservation. Maisie and colleagues, 2011, measured the reaction of beholders to discover how to reintegrate a highly damaged painting by John Martin at Tate Britain. We assume that in the future eye tracking will have significant implications in decisions about art display, museum and exhibition design, and for art educational programs. Fifthly, while almost all research on the psychology of visual art has focused on the perception of art, experimental research on art production, as Mial and Jalenko 2001, still remains a greater challenge. However, it is conceivable that even in this field eye tracking for instance of a painter at work will give us clues in the future about the nature of the creative act. 6.1 Introduction phases are central to human social interaction and their aesthetic valuation has important and wide-ranging societal implications. For example, facial attractiveness is likely to be key to determining mate choice. Thornhill and Gangestad 1999, and it can predict performance across many domains. Langlois et al. 2000, including income and success in job interviews. Titboy et al. 1977, Fries et al. 1991. Comparisons across individuals as well as across different cultures show some variation in what is considered to be attractive. Bruce and Young 1998, yet there is also cross-cultural agreement. Jones and Hill 1993, as well as converging evidence from studies in infants that perception of attractiveness has a strong innate component. Langlois et al. 1987, Slater et al. 1998. Ultimately, it is likely that what is perceived as attractive in a face generalizes across race, gender, and age. Langlois et al. 1991. Mechanisms for evaluating the attractiveness of other people's faces have been widely investigated in the fields of social and experimental psychology, and more recently there have been focused neuroscientific attempts to delineate the brain processes facilitating the evaluation of attractiveness. This chapter will focus on findings from a group of studies performed over the last 10-15 years with the aid of functional brain imaging technologies, including functional magnetic resonance imaging, fMRI, positron emission tomography, PET, electroencephalography, EEG, and magnetoencephalography, MEG, as well as studies of patients with focal brain lesions. Our aim has been to outline what is currently known about the neural mechanisms for evaluation of facial attractiveness, undertake a critical appraisal of the key publications in this field, and discuss how this endeavor contributes more generally to the study of neuroaesthetics. We briefly preface our discussion of the neuroscientific data with a summary of the known physical determinants of attractiveness, section 6.2. Additionally, we outline several relevant theoretical frameworks that have informed the neuroscientific study of attractiveness, section 6.3, before moving on to discuss the relevant studies themselves, section 6.4 and 6.5. 6.2 What makes a face attractive? There have been a number of theories regarding the physical determinants of facial attractiveness. Perhaps the oldest of these relate beauty to optimal proportions between various 112 Skosgethoff and Joel S. Winston facial features. Plato and Leonardo da Vinci, amongst others, were proponents of these theories. A brief account is provided by Bruce and Young, 1998, p. 131. An evolutionarily driven, adaptationist perspective is that facial attractiveness judgments are based on phenotypic characteristics that accurately reflect an individual's health and fitness to their particular environment and its demands. For review see Johnston 2006, Rhodes 2006, Thornhill and Gangestad 1999. In other words, this account posits that facial beauty reflects the reproductive quality of the owner of the face, Senior 2003. There are features that reflect health fairly transparently, including clear eyes, smooth and even-toned skin, and an average body mass index, and clues to many of these can be found in the face. 3 other physical properties of faces that have received special attention in terms of their impact on attractiveness are symmetry, averageness, or typicality, and sexual dimorphism. A detailed review of evidence relating to each of these areas is beyond the scope of this chapter. However, each will be covered briefly in the following paragraphs in the interest of providing an outline of the kinds of physical characteristics that may need to be encoded by neural processes for evaluating attractiveness. Undoubtedly, there are other determinants of facial attractiveness among the physical features and configurations of human faces, besides those already discussed. In addition, other information, both inside the visual domain, e.g. shape of body parts, overall physical condition, and body movement, and beyond, e.g. smell, voice, certainly makes important contributions to attractiveness judgments in real-life situations. However, a broader discussion of these other determinants of human attractiveness is outside the scope of this chapter. 6.2.1 Symmetry. Certain facial traits, which are normally symmetrical, can become less so in some individuals. This phenomenon, termed fluctuating asymmetry, arguably reflects increased sensitivity to genetic and environmental stresses. Moore and Pomiankowski 1993. This idea has been offered as a basis for explaining the link between facial symmetry and attractiveness in evolutionary terms. Thornhill and Gangestad 1999. Faces which are more symmetrical are found more attractive because, according to this account, they suggest the bearer is more robust in dealing with environmental stressors. A number of studies have shown that increasing facial symmetry using computer manipulations leads to increased attractiveness ratings. Herbert et al. 1999, Rose et al. 1998. It is important to note, however, that there is evidence that symmetry co-varies with other facial features such as reduced face length and increased cheekbone prominence. These may also be important determinants of judgments about attractiveness, and therefore the amount of variance in attractiveness accounted for by symmetry alone may be small. Thornhill and Gangestad 1999. Investigation into the brain areas which process facial symmetry has been conducted using fMRI. Chen et al. 2007. Faces activated a number of brain regions in the well-established face processing network. Paxby et al. 2000. See section 6.3.1, including the fusiform face area, the occipital face area, the middle occipital gyri, and the superior temporal and intra-occipital sulci. Symmetrical versions of the faces cause differential activation only in the neural mechanisms for evaluating the attractiveness of faces 113 right occipital face area, suggesting a role for this region in facial symmetry processing. 6.2.2 Typicality. It can be argued from an evolutionary perspective that the most typical faces, which are close to the mean of the population, should be favored as they denote genetic heterozygosity. Thornhill and Gangestad 1999. Indeed, there is empirical evidence that computer-generated composite, average, faces are rated as more attractive than real-life individual faces, Langlois and Rodman 1990, and that this is independent of the increase in facial symmetry that such manipulations can produce. Rhodes et al. 1999. It has been claimed that infant preference for attractive faces may also in fact reflect a preference for typical faces. Rubenstein et al. 1999. However, averageness only increases attractiveness to a point, and specific non-average features can make faces even more attractive. Thornhill and Gangestad 1999. An alternative account to explain differential responses to attractiveness in terms of typicality posits that faces are indexed by their similarity to unfit or disfigured faces, and that disfigured faces thus anchor the lower end of the attractiveness dimension. This view places more importance on the negatively valenced half of the attractiveness scale and proposes that viewing a face as unattractive can be conceptualized as an overgeneralization of mechanisms for representing an unfit face. See Browitz and Montefiore 2008. 6.2.3 Sexual dimorphism. One prevalent argument is that a strong contribution of secondary sexual characteristics to facial features, e.g. wider mandible and prominent eyebrow ridges in men, or enlarged lips and upper cheeks in women, has an asymmetric effect on judgments of attractiveness of faces of men and women. Specifically, feminized female faces are judged as more attractive, while masculinized male faces are perceived as more dominant and dishonest but less attractive, and feminized male faces are instead preferred. Herbert et al. 1998. A possible explanation for this finding is that feminized male faces predict more cooperative, honest, and caring behavior, and may thus indicate willingness to invest in a long-term and stable relationship. The preference for feminized male faces is by no means a universal finding, however. Further work has shown that in fact, women prefer feminized male faces only when in the less fertile phase of their menstrual cycle, and preference shifts to more masculine faces during the more fertile phase. Tentenboek et al. 1999. In addition, the shift towards preference for masculinized male faces during the fertile phase of the menstrual cycle was abolished when women were instructed to select specifically long-term male partners. Tentenboek et al. 1999. A number of other studies have found that sex-specific facial features are significantly predictive of attractiveness judgments. Cunningham 1986, Cunningham et al. 1990, Johnston and Franklin 1993. But caution must be exercised given the variability of judgments, particularly in women, depending on cyclical fertility or the specific purpose of face choice. 6.3 Conceptual frameworks for studying brain processing of facial attractiveness. 6.3.1 Distributed neural systems for face perception. Faces are highly complex visually, as well as highly socially informative, and it is therefore no surprise that face perception has received a great deal of attention in the neurosciences. For some years, the most influential cognitive model of face perception has been that of Bruce and Young, 1986, which emphasized distinct processing streams to deal with different kinds of information relevant to faces. A key distinction was made between processes supporting identity recognition and those supporting recognition of facial expressions and speech. The advent of fMRI allowed brain areas involved in facial processing to be determined with considerable anatomical specificity, leading to influential findings of activation by faces of an area in the fusiform gyrus, subsequently named the fusiform face area, FFA, Ken Wisher et al. 1997, as well as an area in the superior temporal sulcus, STS, e.g. Puce et al. 1998, amongst others. Such findings have since been widely replicated and have fueled the development of an influential neurobiological framework describing human face perception, Paxby et al. 2000. Paxby and colleagues extended Bruce and Young's model by proposing, with new anatomical specificity guided by neuroimaging findings in humans and neuronal recordings in non-human primates, a core system for face perception made up of the inferior occipital gyri, or occipital face area, OFA, facilitating visual analysis of facial features, FFA, facilitating face recognition, or analysis of invariant face information, and STS, facilitating processing of the dynamic aspects of faces such as expression and eye gaze. The model also describes interactions between this core system and an extended system that includes regions involved primarily in other cognitive functions, but which make important contributions to face perception, such as the amygdala, emotion evaluation, and anterior temporal cortex, retrieval of biographical information. Subsequent studies of face perception have largely adopted this framework, and it anchors much of the research into the neural processing of facial attractiveness also. At the same time, it is important to note that while the overall concept of dual streams of core face processing, invariant and dynamic, has been very powerful in framing work in this field over the last 10-15 years, it is increasingly apparent that there is considerable crossover in the roles of the two processing streams, and they are far from completely dissociable. For example, there is evidence for the involvement of STS in representing facial identity, Winston et al. 2004, as well as involvement of the FFA in representing facial expression, Fox et al. 2009. A detailed critique of the separate face processing pathways has previously been undertaken, along with proposals of alternative models, Calder and Young 2005. In particular, the role of STS is probably much broader than simply covering dynamic aspects of faces, and the region has been reframed as being involved in evaluation of the social relevance of faces, especially in terms of inferring the goals and intentions of others. Allison et al. 2000, these conveyed by dynamic or static signals. Neural mechanisms for evaluating the attractiveness of faces. 115 6.3.2 Attractive faces as rewarding stimuli. Another common framework within which to place investigation of the neural processing of facial attractiveness conceptualizes faces as rewarding stimuli, or as positive reinforcers, i.e. stimuli which encourage behaviors that are associated with their perception. Examples of behavioral modulation by facial attractiveness lend support to this view. However, it has been pointed out that unlike drives towards food, water, or warmth, a drive towards attractiveness cannot arise from a deficit state, Aharon et al. 2001. In addition, it has been proposed that faces with an adaptive value, e.g. opposite-sex faces, are processed as rewarding, whereas those without such value, e.g. beautiful same-sex faces, are instead processed as aesthetically pleasing, but not as rewarding. Senior 2003. The well-established reward circuit that guides approach and avoidance behaviors has the striatum, caudate, putamen, and nucleus accumbens at its core, but it also includes important anatomical connections between the striatum and midbrain nuclei such as the ventral tegmental area, as well as orbitofrontal, ventromedial, and ventrolateral prefrontal cortex, and limbic structures such as the amygdala. Delgado 2007. The involvement of this circuit in the processing of facial attractiveness now has considerable empirical support from fMRI studies. Aharon et al. 2001, Liang et al. 2010, O'Doherty et al. 2003, Winston et al. 2007, and this is discussed in more detail in section 6.4.1. Whether attractiveness is always processed through reward circuitry in the brain, or this is only the case for extremely attractive faces, Menziglevsky et al. 2012, and perhaps extremely unattractive faces, Liang et al. 2010, remains debatable. Besides extremes of attractiveness or unattractiveness, it has also been suggested that specifically making attractiveness evaluation a goal, Mency-Lutsky et al. 2012, or the presence of other social cues, such as gaze direction, that may indicate a favorable or unfavorable engagement with an attractive face, Camp et al. 2001, may contribute importantly to activation of reward systems. 6.3.3 Attractiveness as a trait. Commonality with mechanisms of facial emotion recognition. Another way of conceptualizing facial attractiveness is a trait exhibited by faces, in common with other traits such as trustworthiness, aggressiveness, and confidence. When people are asked to provide unconstrained descriptions of real-life face images, attractiveness is the most commonly used descriptor, Oosterhoff and Todorov 2008, which presumably reflects the high evolutionary importance of this trait. On the other hand, Oosterhoff and Todorov 2008 found that different trait descriptions of faces were highly intercorrelated and used principal components analysis to show that evaluation of faces based on such traits can be described by a two-dimensional conceptual space, with axis of dominance and trustworthiness, the latter approximating to valence. Todorov and colleagues have gone on to argue that there are common neural mechanisms subserving evaluation of different facial traits, as well as evaluation of facial emotional expressions, said et al. 2011, which is consistent with emotion overgeneralization hypotheses, Zebrowitz 2004. Behaviorally, it has been shown that ratings of faces according to 116 Sposketoff and Joel S. Winston traits and ratings according to emotional expressions are frequently intercorrelated. For example, faces rated as highly dominant by one sample of participants are consistently rated as angry by an independent sample, said et al. 2011. In addition, principal components analysis shows that emotion and trait judgments have very similar dimensional structures, said et al. 2011. Finally, evidence for commonality of neural mechanisms for emotion and trait judgments comes from an adaptation study, Engel et al. 2010, demonstrating that neutral faces were judged as more trustworthy after adaptation to angry faces and less trustworthy after adaptation to happy faces, suggesting commonality in mechanisms for processing trustworthiness with those for anger and happiness. These behaviorally demonstrated commonalities, while not direct evidence of common neural mechanisms, are at least suggestive of commonalities in the neural evaluation of facial traits and expressions. Further support for this claim can be found in neuroimaging findings, which have established a similarity in the brain regions active during evaluation of attractiveness and trustworthiness. Stock et al. 2010, Mency-Lutsky et al. 2012, Winston et al. 2007, 2002, and during evaluation of untrustworthy and angry faces, Mency-Lutsky et al. 2012. Commonality of mechanisms for facial expression and facial trait processing could clearly be a very useful framework for understanding facial attractiveness evaluation, particularly given the comparatively well-developed understanding of neural mechanisms for evaluation of emotional facial expressions, reviewed by Bluemere and Portois 2007. At the same time, some dissociation of mechanisms is highly likely, with some regions or networks being involved specifically in one aspect of social face processing only. 6.3.4 Distance from mean and valence space. An alternative view, related to that discussed in section 6.3.3, again hinges on placing attractiveness within a two-dimensional space described by axis of valence and dominance, Oosterhoff and Todorov 2008, said et al. 2011. There is evidence to suggest that neural responses to faces, for example in the amygdala, may represent distance from typicality in valence space, rather than evaluation of any specific social dimension, said et al. 2010. Viewed within this framework, inconsistencies and findings from different studies of the neural correlates of attractiveness can be explored, and at times explained, through differences in the typicality of the face stimuli used. More specifically, this theory predicts that whether the stimulus sets used in a study have placed most typical faces in the center of the attractiveness dimension or at one extreme of it could have important implications for the results. Mency-Lutsky et al. 2012, said et al. 2011. For example, the use of naturalistic face photographs, e.g. Udorty et al. 2003, leads to the most typical faces being at the positive end of the attractiveness continuum, leading to a linear typicality function, and correspondingly, to mainly linear neural responses, said et al. 2010. In contrast, synthetic face stimuli, e.g. Chatterjee et al. 2009, Kim et al. 2007, would tend to have a nonlinear typicality function, with the most typical faces in the middle of the continuum, and thus result in nonlinear neural responses. See figure 6.1 for examples of naturalistic and computer-generated face images used in studies of facial attractiveness. Whether this is an entirely accurate claim remains open to debate, but it could certainly be useful in guiding attempts to interpret discrepancies between the results of different studies. Neural mechanisms for evaluating the attractiveness of faces. 6.3.5 Neuropsychological models of aesthetic preference. Neuroaesthetics, a term pioneered by Zicke, 1999, has been defined as the neural underpinnings of aesthetic experience of beauty, particularly in visual art, Didio and Galiz 2009. As in other spheres of social life, faces have an important place in art. An understanding of the neural mechanisms for evaluating facial attractiveness will help explain specifically how we ascribe aesthetic value to faces, but it is also of much broader relevance to the study of neuroaesthetics, with the potential to provide clues to any neural mechanisms shared by all aesthetic experience. It is therefore important to consider how studies of the neural correlates of aesthetic and/or attractiveness evaluation of faces can be framed using neuropsychological models of aesthetic preference. A recent review tackling this issue, Nadal et al. 2008, evaluates models of the processing steps involved in figure 6.1 examples of face stimuli used in studies of facial attractiveness evaluation. Panel A shows several highly attractive faces, half of which have a mildly smiling expression and the other half a neutral expression. Faces were obtained from photographs in magazines. Panel B shows an example of computer-generated faces, with one identity on the left-hand side, another on the right, and morphs, in percentage change from the left-hand identity, in the middle. Participants were asked to judge how attractive each face was. Determining the aesthetic value of a stimulus, with particular reference to a model proposed by Chatterjee, 2003. Chatterjee posited three processing stages relevant to the hierarchy of perceptual processing in general: early processing to extract and analyze simple visual components, intermediate level processes to segregate or group elements, and late processes where key aspects of the stimulus can be integrated with relevant memories and emotions. Such a framework can facilitate the integration of aesthetic theory with relevant neurobiological findings, and reference will be made to this when discussing neurobiological findings in section 6.4 and 6.5 of this chapter. Notwithstanding the utility of such models, it is important to bear in mind that they are rarely likely to describe fully and accurately the interplay of all relevant neural processes. For example, it is well known that emotive aspects of faces influence both early and late processing components. Eimer and Holmes 2002, Sato et al. 2001, and an early component of emotional processing does not fit neatly into the cognitive model described here. As discussed in more detail in section 6.4.4, facial attractiveness also modulates both early and late components of neural processing. Van Hook et al. 2011, Warhide et al. 2007. 6.4 Studies of the neural mechanisms for evaluating facial attractiveness. 6.4.1 Involvement of the brain's reward circuitry in evaluation of facial attractiveness. The earliest investigation into neural mechanisms for evaluating facial attractiveness made use of PET and demonstrated involvement of left frontal cortical regions. Increased regional cerebral blood flow, RCBF, in left anterior frontal cortex was correlated with judgment of faces as unattractive, and increased RCBF in the left frontotemporal junction was correlated with judgments of faces as attractive. Nakamura et al. 1998. Subsequently, a number of studies have used fMRI to explore the neural correlates of attractiveness evaluation with greater anatomical specificity. Much of this early work has been guided by the framework that tests attractive faces as stimuli that engage the brain's reward processing systems, as discussed earlier in section 6.3.2. Aharon and colleagues, 2001, hypothesized that there are separable neural mechanisms for aesthetic assessment of attractiveness in faces, termed liking, and for driving motivated behavior in relation to attractive faces, termed wanting. Separate groups of heterosexual males either rated the beauty of faces, a mix of neutral and attractive faces of each gender, or pressed a key to prolonged viewing of the same set of faces. Participants rated both attractive males and females as such, but exerted effort specifically and only to prolong viewing of attractive females. A third group of males underwent fMRI during passive viewing of the same set of faces. There was a significant interaction between attractiveness and face gender in the nucleus accumbens, an area strongly associated with reward processing, e.g. Bardo 1997, Knudsen et al. 2001. This interaction was driven by stronger activations to beautiful female faces and average male faces than to beautiful male faces or average female faces, figure 6.2d. Other regions of interest, including neural mechanisms for evaluating the attractiveness of faces mean stimulus-related neural activation, from studies highlighting brain regions that respond differentially to varying levels of facial attractiveness. Panel A gives an example of stimuli used, from left to right, beautiful female face, average female face, beautiful male face, average male face. Panel B shows the attractiveness ratings, on a scale of 1-7, given for each of the 4 categories of face from Panel A, by a sample of male participants. Panel C shows average viewing time, increased by pressing a button repeatedly, achieved for each of the 4 face categories from Panel A, by a separate sample of male participants. Panel D shows blood oxygen level dependent fMRI signal change in the nucleus accumbens, NAC, for each of the 4 face categories depicted in Panel A. Figure 6.2ad are reprinted from Neuron 32, 3, Itzhak Aharon, Nancy Itkoff, Dan Early, Christopher F. Chabris, Ethan O'Connor, and Hans C. Rader. Beautiful faces have variable reward value, fMRI and behavioral evidence, pages 537-551, copyright 2001, with permission from Elsevier. Panel E shows the main effect of attractiveness, high attractiveness, low attractiveness, in medial orbitofrontal cortex, OFC, posterior cingulate, and medial prefrontal cortex, MPFC. Reprinted from Neuropsychology, 41, 2, J. O'Doherty, J. Winston, H. Critchley, D. Purwitt, D.M. Burt, and R.J. Dolan, Beauty and a Smile, The Role of Medial Orbitofrontal Cortex in Facial Attractiveness, pages 147-155, copyright 2003, with permission from Elsevier. Numbers in top left corner of brain images show relevant coordinate, X coordinate for sagittal images, Y coordinate for coronal images, of the displayed slice. 120 Spozgethoff and Joel S. Winston sublenticular extended amygdala, SLEA, and ventral tegmental area, VTA, also showed strong activations associated with viewing of attractive female faces, but no differential activation for average and attractive male faces. The pattern of activation in SLEA and VTA was noted to mirror closely results of the key pressing behavioral task. In summary, the results suggest some dissociation between liking and wanting behaviorally. Both attractive male and female faces are liked, but only attractive female faces are wanted by heterosexual males. In terms of neural activation, such a dissociation is less clear. No brain areas mirrored the liking pattern of behavioral results, but areas important for reward processing did mirror the wanting pattern of behavioral results. The most significant and noteworthy findings were in the nucleus accumbens, suggesting that it may play an important role in distinguishing attractive and rewarding faces from attractive and unrewarding ones. In order to resolve whether neural processes signaling attractiveness evaluation can be dissociated from those engaged by reward expectation, O'Doherty and colleagues, 2003, performed an fMRI experiment with an event-related design point. 1. The authors found activation in the medial orbitofrontal cortex, OFC, during viewing of attractive faces, while more lateral prefrontal regions, including lateral OFC, were responsive to unattractive faces, figure 6.2e. These findings reflect implicit evaluation of attractiveness because participants were unaware that attractiveness was the critical experimental measure and were asked to determine the gender of each presented face, rather than to rate attractiveness directly. In addition, half of the stimulus set was made up of mildly smiling faces, which resulted in further enhancement of OFC activity. The key findings were thus that OFC is engaged automatically by attractive faces, and that this engagement is positively modulated by happy facial expression. Results showing activation of lateral OFC by unattractive faces and / or medial OFC by attractive faces have since been replicated. Cloutier et al. 2008, Hampshire et al. 2012. Further work has extended the conceptualization of attractive faces as rewards by establishing involvement of the amygdala, which plays an important role in evaluation of social stimuli. See Adolphs 2010 for a review. Winston and colleagues, 2007, hypothesized that the amygdala would show nonlinear changes in blood oxygen level dependent, both, fMRI responses to attractiveness, with higher responses to both attractive and non-attractive, relative to neutral, faces. This would explain why previous work, seeking only linear relationships between brain activity and attractiveness, found no activation in the amygdala. The author's findings were consistent with this hypothesis, additionally showing nonlinear and linear responses to attractiveness in different regions of OFC. This study also compared neural responses during implicit attractiveness judgments, while evaluating gender, with those during explicit attractiveness judgments. Explicit judgment of attractiveness recruited a network including medial prefrontal and paracingulate cortices, posterior OFC, infla, and STS. Nonlinear neural responses to facial attractiveness have been found in other regions of the established reward processing network, including anterior cingulate cortex, ACC, lateral OFC, striatum, including nucleus accumbens, caudate, and putamen, and VTA neural mechanisms for evaluating the attractiveness of faces. Task-related neural activation, from studies highlighting brain regions that respond differentially to attractiveness evaluation or an alternative control task. Panel A shows superior temporal sulcus, STS, and prefrontal responses for attractiveness judgments, contrasted with age judges. There are 4 individual loci of activation in STS, labeled 1-4, 2 on each side of the brain, and 3 individual loci of activation in prefrontal areas, labeled 5-7. Reprinted from Neuropsychology, 45, 1, Joel S. Winston, John O'Doherty, James M. Filner, David A. Purwitt, and Raymond J. Dolan, Brain Systems for Assessing Facial Attractiveness, pages 195-206, copyright 2007, with permission from Elsevier. Numbers in top right corner of brain images show relevant coordinate, X coordinate for sagittal images, Y coordinate for coronal images, Z coordinate for axial images, of the displayed slice. Panel B shows neural responses to facial beauty, contrasted with facial identity, left, and to facial identity, contrasted with facial beauty, right. Black-colored areas represent increased responses to attractive faces and white-colored areas represent increased responses to unattractive faces. Reprinted from Neuropsychology, 23, 2, Anjan Chatterjee, Amy Thomas, Sabrina E. Smith, and Jeffrey K. Gear, The Neural Response to Facial Attractiveness, pages 135-43, doi, 10.1037/00144330 copyright, 2009, with permission from the American Psychological Association. Panel C shows blood oxygen level dependent signal change in right fusiform face area, RFFA, and right STS, RSTS, during evaluation of attractiveness, explicit condition, or one-back stimulus identification task, implicit condition. Reprinted from Journal of Neuroscience, 155, 2, Giuseppe Ria, Christopher J. Fox, Christopher T. Waite, Itzhak Aharon, and Jason J. S. Barton, The Contribution of the Fusiform Gyrus and Superior Temporal Sulcus in Processing Facial Attractiveness, Neuropsychological and Neuroimaging Evidence, pages 409-22, figure 8, doi, 10.1016/j.neuroscience.2008.05046 copyright, 2008, with permission from the Society for Neuroscience. 122 Spozgethoff and Joel S. Winston, Liang et al. 2010. Stimuli used by Liang and colleagues included extremely unattractive and disfigured faces, in line with the overgeneralization account for unattractiveness processing already described in section 6.2. See Browitz and Montefiore 2008. Besides supporting a view of attractive faces as rewarding, these findings go further by proposing that faces varying on the attractiveness dimension in either direction should be viewed as motivationally salient, and that there is widespread processing of both attractive and unattractive stimuli within the same regions. Further support is lent to the view of attractive faces in the context of reward and reinforcement by a study which explores the capacity of attractive faces to influence behavioral preference, Brand and O'Doherty 2007. The authors show that it is possible to establish classical conditioning by pairing visual stimuli with subsequent presentation of attractive or unattractive faces. In a group of participants of both genders, changes in behavioral responses to the conditioned stimuli were observed specifically when they were paired with attractive female faces. When responses were modeled in terms of reward prediction error, such error correlated with ventral striatal activity during conditioning with attractive faces. These findings closely parallel previous findings with monetary rewards for the provision of juice to thirsty participants, McClure et al. 2003, O'Doherty et al. 2004, and suggest that attractive faces may indeed be treated as other rewarding stimuli by the brain. In sum, the hypothesis that attractive faces are rewarding has received support from a growing body of functional imaging evidence, which delineates a network of both cortical and subcortical structures. This network has most consistently included the nucleus accumbens in OFC. Some areas, e.g. STS and medial prefrontal cortex, are differentially activated by implicit and explicit evaluation of attractiveness. Some reward processing regions, including OFC, encode facial attractiveness in both a linear and nonlinear fashion, while others, most notably the amygdala, appear to respond specifically in a nonlinear manner. The conceptualization of attractive faces as rewarding stimuli has been a fruitful one, and some dissociation between neural determinants of pure aesthetic evaluation versus motivated behavior in relation to attractive faces has been demonstrated. 6.4.2 Processing of attractive faces as high-level visual stimuli. A number of neuroimaging studies have sought to explore evaluation of facial attractiveness by focusing on engagement of brain areas specialized for visual processing, rather than on areas for reward processing. While there is clearly overlap between the neural processes that underlie these two aspects of facial attractiveness evaluation, and neither is likely to proceed in complete isolation from the other, each has been investigated using distinct experimental questions and approaches. In a study by Chatterjee and colleagues, 2009, use was made of computer-generated face images, which were equated in terms of distinctiveness from an average face, figure 6.1b. This is a notably different approach from the studies discussed in section 6.4.1, all of which used naturalistic stimuli. The authors found that explicit attractiveness judgments activated a network including anterior insula, dorsal posterior parietal cortex, and inferior and medial prefrontal regions. We note considerable overlap with the findings neural mechanisms for evaluating the attractiveness of faces 123 of Winston et al. 2007. In addition, ventral occipitotemporal areas, including FFA and lateral occipital cortex, were also widely activated, figure 6.3b. Importantly, Chatterjee and colleagues, 2009, were able to show that activity in many of these regions varied parametrically with degree of facial attractiveness. Only the ventral occipitotemporal areas remained active during implicit attractiveness evaluation. Participants were judging facial identity instead, figure 6.3b. The conclusion was that the outlined ventral occipitotemporal network is triggered automatically by attractiveness. Urea and colleagues, 2008, asked a more specific question about which structures in the core system for face perception, traditionally held to incorporate parallel processing routes via FFA and STS, as described in detail in section 6.3.1, see also Haxby et al. 2000, are most important in the processing of attractiveness in faces. Given the strong social relevance of facial attractiveness, one might predict a key role for STS, although given that attractiveness is a largely invariant trait, one might instead argue that structural features, predominantly processed in FFA, would be more important. In the first experiment, the authors investigated how attractiveness judgments and attractiveness-motivated behavior differed between 8 patients with acquired prosopagnosia, a deficit in recognizing personally familiar faces caused by damage to occipitotemporal cortex, usually including FFA, figure 6.4, and 19 healthy controls. Prosopagnosic patients were impaired in both types of task, and the degree of each individual's impairment correlated with severity of their face recognition deficit. However, half of the patients showed some residual ability to appropriately rate attractiveness. 2 of these had bilateral anterior temporal lesions, one with clear sparing of right FFA and STS, and the other 2 had unilateral right occipitotemporal lesions, one with clear involvement of right FFA. The authors conclude that the correlation between severity of prosopagnosic deficit and degree of impairment of attractiveness evaluation supports the involvement of identity-related processing in attractiveness evaluation. The majority of patients scored either normal or near normally on emotional expression recognition testing, and only 2 patients had lesions clearly involving STS. It is therefore difficult to make any strong inferences about importance of STS from these data. More generally, difficulty in interpreting the results stems from the heterogeneous sample with respect to lesion location, figure 6.4, which precludes the possibility of ascribing the attractiveness evaluation deficit to a single anatomical structure, or set of structures. In a separate fMRI study, healthy participants viewed faces varying in attractiveness and either performed explicit evaluation of attractiveness, or performed an unrelated task, in which case attractiveness evaluation was considered implicit. Notably, the implicit task used here, a one-back task requiring matching of each face to the last presented face, differed substantially to those used in other studies discussed earlier, which required age or gender judgments, Winston et al. 2007, Chatterjee et al. 2009, and this may contribute to differences in the results. Urea and colleagues, 2008, found that while FFA activation was not correlated with degree of attractiveness, such activation did increase bilaterally during explicit, as compared to implicit, evaluation. STS showed greater activity during implicit than during explicit evaluation, figure 6.3c. Moreover, activation was increased in a network including OPA, amygdala, and OFC during explicit processing 124 Spotsgethoff and Joel S. Winston of attractiveness. The findings from both the neuropsychological and fMRI experiments of Urea and colleagues, 2008, are consistent with the role for FFA in facial attractiveness evaluation, although it is difficult to draw more specific conclusions about relative importance of FFA and STS, particularly given the variability of patients' lesion extent and location. As discussed in section 6.3.1, there is substantial evidence of overlap between the function of the invariant, FFA-related, and dynamic, STS-related, streams of face processing even in healthy individuals, and such overlap may occur to an even greater extent as the result of remodeling in the wake of structural brain lesions. Facial attractiveness processing has also been investigated in patients with congenital prosopagnosia, a condition of significantly impaired face recognition from birth, Behrman and Abaidon 2005. By definition, such individuals have no clear associated structural brain lesion visible on imaging, although recent studies have found more subtle figure 6.4 example lesion study, which address the involvement of the distributed brain system for face perception and evaluation of facial attractiveness. Structural Mr. Brain images from 7 of the 8 prosopagnotic patients tested by Urea et al. 2008 are shown. The number at the top left of each set of images is an individual patient identifier. The heterogeneity of lesion location is clearly evident. Reprinted from the Journal of Neuroscience, 155, 2, Giuseppe Urea, Christopher J. Fox, Christopher T. Waite, Itzhak Aharon, and Jason J. S. Barton, the contribution of the fusiform gyrus and superior temporal sulcus in processing facial attractiveness, neuropsychological and neuroimaging evidence, pages 409-422, figure 1, doi, 10.1016/j.neuroscience.2008.05.046 copyright, 2008, with permission from the Society for Neuroscience. Neural mechanisms for evaluating the attractiveness of faces. 125 regional differences in gray matter volume when compared to non-prosopagnotic brains. Dinkelacker et al. 2011. Garrido et al. 2009. Adding to the findings of Uria and colleagues, 2008, one study found that ability to make accurate attractiveness judgments was usually impaired in patients with congenital prosopagnosia. L. E. Brand et al. 2006. On the other hand, two studies have found that ability to rate attractiveness is preserved in at least some patients with congenital prosopagnosia, despite impairments in face recognition. Sadr et al. 2004, or rating of distinctiveness. Carbon et al. 2010. These findings would suggest that processing of facial identity and facial aesthetic value are dissociable at least in some cases. These results appear highly informative for cognitive models of attractiveness and facial processing more generally. It must be noted, however, that congenital prosopagnosia is a heterogeneous condition with respect to individual behavioral deficits, and this presumably also applies to heterogeneity in neural deficits. The relative importance of FFA and STS, and other core brain regions involved in the perception of faces, in evaluation of facial attractiveness remains an intriguing question for further investigation. It is important to note that there are grounds to expect that regions for both static and dynamic aspects of face processing would be involved in attractiveness evaluation. First, it is clear that attractiveness is influenced by both structural properties, such as symmetry, and more dynamic signals, such as gaze direction or expression, which may be expected to be processed preferentially by one or the other of these systems, respectively. Secondly, it is increasingly appreciated that there is much more overlap between processing of structural face properties in the FFA and dynamic face properties in the STS than originally appreciated, and the roles of these two streams are not in fact entirely dissociable. Calder and Young 2005. 6.4.3 Meta-analyses of studies investigating neural processing of facial attractiveness. Two recent meta-analyses have combined and reframed results from studies of the neural correlates of facial attractiveness. It is important to note that while meta-analyses of neuroimaging data provide a powerful means of aggregating findings across many studies, which can result in more accurate and robust results, there are important methodological limitations. For review, see Kober and Wager 2010, Radua and Mateo calls 2012. Stock and colleagues, 2010, employed activation likelihood estimation analysis of 16 fMRI studies to investigate the hypothesis that facial attractiveness and facial trustworthiness judgments are processed by overlapping brain networks. In terms of attractiveness evaluation, most consistent neural activation was found in the amygdala, in particular the red amygdala, supporting the now widely postulated extended role of the amygdala in processing motivationally and socially relevant stimuli regardless of valence. Adolphs 2010. In addition, there was convergent activation of medial OFC and inferior frontal gyrus, IFG. The author's interpretation is that the amygdala acts as a filter of evolutionarily relevant sensory information, including information with potential long-term payoffs such as attractiveness. Meanwhile, the medial OFC is proposed to appraise beauty as indexed by reward value, while IFG processes semantic aspects of faces. A nucleus 126 Fosgatoff and Joel S. Winston accumbens response to attractive faces was found in a number of neuroimaging studies, and this structure was therefore also posited to play an important role in attractiveness evaluation. A second meta-analysis by Menzibletsky and colleagues, 2012, again focused on studies that have used neuroimaging methods to investigate the neural correlates of attractiveness and/or trustworthiness evaluation, but using an alternative methodology, multi-level kernel density analysis. The authors included a larger number of studies than did Stock and colleagues, 2010, with a total of 29 studies analyzed, 17 specifically focusing on the neural basis of attractiveness evaluation. While both meta-analyses report similar inclusion criteria, the work by Stock and colleagues, 2010, excluded a number of studies based on unobtainable brain coordinates of results, restriction of findings to regions of interest defined a priori, or experiments that were deemed unsuitable for their analysis. Many of these studies were included in the analysis of Menzibletsky and co-workers, 2012, alongside a handful of studies published later than the meta-analysis of Stock and colleagues, 2010. It is important to bear in mind these sampling differences and the differing analysis methodologies when comparing the results. Across both attractiveness and trustworthiness, the findings of Menzibletsky and colleagues, 2012, were that activation patterns systematically vary as a function of face valence, bilateral amygdala for negative faces, and a network including left caudate and extending into the nucleus accumbens and medial OFC, as well as ventromedial prefrontal cortex, perigenual ACC, and right thalamus for positive faces. A key component of the analysis conducted by Menzibletsky and colleagues, 2012, concerned neural responses that vary with stimulus valence nonlinearly, e.g. with stronger responses to both positively and negatively valenced faces compared to neutral. Such nonlinear responses were found in the right amygdala, extending into the right putamen. Furthermore, the authors proposed that results of their analysis support a functional fractionation of the right amygdala into a ventral portion with linear responses to negatively valenced faces and a dorsal portion with nonlinear responses to socially relevant faces. Focusing on attractiveness specifically, no regions active during evaluation of unattractive faces were reported. However, attractiveness research has focused much more on the effect of positively valenced, attractive faces, and evaluation of these is reported to activate a network including the left caudate, nucleus accumbens, ventromedial prefrontal cortex, VMPFC, OFC, and perigenual ACC with significantly more consistency than for trustworthy faces. Menzibletsky and colleagues, 2012, comment that the use of extremely attractive faces, e.g. culled from magazines, in some studies and not in others, could explain an important discrepancy found within the facial attractiveness literature. They argue that studies showing activation in reward-related areas including nucleus accumbens, caudate, and medial OFC, have made use of faces possessing extremely attractive features, e.g. O'Doherty et al. 2003, as well as extremely unattractive ones, Liang et al. 2010. In contrast, computer-generated faces, often used in studies that have failed to show involvement of reward-related regions, e.g. Chatterjee et al. 2009, tend to show variation of valence in both directions from an averagely attractive face. Furthermore, faces at the extremes of the neural mechanisms for evaluating the attractiveness of faces. 127 attractiveness dimension tend not to be included in such studies. While it is possible that only extremely attractive or unattractive faces are treated as rewarding or aversive, and straight all reward systems are only engaged in such contexts, we suggest an alternative interpretation could be that computer-generated faces are often not placed in the same context as naturalistic faces. It seems intuitive that a naturalistic face could more easily be imagined to belong to a potential mate than a computer-generated face. Whether such a distinction holds is also likely to be dependent on the experimental task and overall context, since reward regions may respond with the same strength to rewards of very different magnitude providing they are placed in different contexts, e.g. Togler et al. 2005. A related possibility is that experimental paradigms that make use of participant samples from one gender only, and expose them specifically to face stimuli of the opposite gender, may automatically create a more mate-seeking context in which attractive faces of opposite gender become rewarding in a way that they are not in a purely evaluated context. Cloudier et al. 2008. These are intriguing possibilities, but they are yet to be evaluated empirically. 6.4.4 Neurophysiological studies of the processing of facial attractiveness. This chapter focuses primarily on evidence for neural processing of facial attractiveness obtained using fMRI. While such studies form by far the most numerous, as well as most highly cited, group of research outputs on this topic, it is important to remember that fMRI has a number of limitations as a method for studying neuronal function. Two of these limitations, namely, Rie's modest temporal resolution, and the indirect relationship between threefold signal and neuronal activity in the brain, are well addressed by EEG and May, which provide far superior temporal resolution and a more direct measure of neuronal function. Findings from studies employing such neurophysiological methodologies are therefore often complementary to findings obtained using fMRI. In the light of this, we will briefly review the contribution of neurophysiological methodologies to the understanding of neural processing of facial attractiveness. An early EEG study on this topic, undertaken over over 15 years ago, made use of computer-generated faces varying in attractiveness, which were shown to heterosexual male participants, Johnston and Oliver Rodriguez 1997. Event-related potential recordings, ERP, representing EEG changes time-locked to stimulus presentation, showed that the amplitude of a late positive component of the signal, around 400-600 ms, was correlated with attractiveness ratings given to female, but not male, faces and was also modulated by the modification of relevant facial features, particularly short lower jaws, full lips, and widely spaced eyes, that also enhanced behavioral ratings of attractiveness. Since the late positive component has been extensively linked with changes in affect, e.g. Farwell and Duncan 1991, this finding was interpreted as a time signature of affective components of attractiveness evaluation. The modulation of the late positive component by facial attractiveness has since been replicated in a study that extended previous findings by demonstrating that variations in facial attractiveness are also associated with modulation of an early posterior negativity, around 150-250 ms, which is temporally distinct from the late positive 128 Spotsgatoff and Joel S. Winston component, and are viewed to reflect evaluation of emotional significance that guides attentional capture. Warhide ETAL 2007. Figure 6.5. A more recent ERP study, Van Hoof ETAL 2011, employed an orienting task to explore attentional bias related to facial attractiveness. Faces were incidental to the experimental task, unlike in the experiments of Johnston and Oliver Rodriguez 1997, and Warhide ETAL 2007, enabling investigation of automatic stimulus-driven facial attractiveness processing. Faces at both ends of the attractiveness scale elicited larger early ERP components. Figure 6.5 event-related potential responses to attractive and non-attractive faces. Faces were preceded by prime images that were either also faces, left side panels, or common everyday objects, right side panels. The results show how facial attractiveness modulates both a late positive component, LPC, of the response, upper panels, and an early positive negativity, EPN, component of the response, lower panels. These modulations occur both when stimuli are primed with faces, left-sided panels, and with objects, right-sided panels. PC and O2 refer to scalp electrode positions from the extended 1020 system, midline parietal and right occipital, respectively. Reprinted from Biological Psychology, 79, 1-2, Kathy Warhide, and Catherine Schacht, and Werner Sommer. Facial attractiveness modulates early and late event-related brain. This finding was proposed to relate to implicit selective attention. The late slow-wave component of the response was more prominent for attractive opposite-sex faces in males but not in females, suggesting that males have a gender-specific mechanism for heightened motivated attention towards attractive female faces. These two ERP components, which occur at different latencies from stimulus onset, presumably reflect different aspects of attractiveness processing. The fact that the signal components show modulation by the attractiveness of task-irrelevant faces adds support to other evidence suggesting that aspects of attractiveness evaluation are automatic. Chaturji ETAL 2009, O'Doherty ETAL 2003, Winston ETAL 2007. Other recent ERP studies have found similar temporal signatures for facial attractiveness evaluation, and in addition report further findings that shed light on attractiveness processing under limited cognitive resources. Rule ETAL 2011, ERP changes corresponding to recognition of attractive faces, Zhang ETAL 2011, and the interaction between attractiveness and cooperative behavior, Chen ETAL 2012. In sum, neurophysiological measures have played an important part in advancing our understanding of the neural mechanisms for facial attractiveness evaluation, largely by helping to establish temporally distinct components corresponding to various aspects of such processing. In addition, many of the principal findings, such as automaticity of processing for attractiveness, and engagement of systems specialized for evaluation of reward or emotion, converge with findings from the fMRI literature. On the other hand, there has been relatively little evidence from the neurophysiological literature to support the notion that attractiveness modulates mechanisms for structural encoding of faces. Future studies using methodologies with high temporal resolution will undoubtedly continue to make an important contribution to this area. 6.4.5 Evaluating facial attractiveness in a social context. As already discussed, faces play an important role in social interaction, and evaluating their attractiveness has wide-ranging societal implications from guiding make choice to influencing decisions about moral character and employability. While several studies discussed in other sections of this chapter address the socially relevant aspects of attractiveness evaluation, and will be again briefly mentioned here, a handful of studies not discussed elsewhere have also directly focused on social aspects of facial attractiveness evaluation. Kulcherov and colleagues, 2009, showed that individual assessments of facial attractiveness are adjusted according to group opinion. Using fMRI, they found that the difference between an individual's decision and the group's decision about the attractiveness of faces was predicted by increased fold response in the rostral zone of cingulate cortex and decreased fold response in ventral striatum. The authors comment that the mechanisms found are analogous to prediction error postulated to underpin reinforcement learning. Besides placing social conformity in the same framework as reinforcement learning, the findings provide specific insight into the impact of group opinion on judgments of facial attractiveness. More recently, a similar question was addressed by Zaki and colleagues, 2011. Here the authors focused specifically on differentiating private acceptance of group opinion, true 130 Spotsgatoff and Joel S. Winston modification of an individual's beliefs, from public compliance, appearing to modify beliefs in order to meet public expectations. For this reason, instead of undergoing fMRI while making initial ratings of facial attractiveness and receiving feedback about group opinion of the same faces, as in Kulcherov ETAL 2009, in this case participants underwent fMRI 30 minutes later, at which time they were asked to rate all previously seen faces on an attractiveness scale for a second time. Stimuli that had been rated as more attractive by peers than by participants resulted in increased activation in the nucleus accumbens and the OFC, as compared to stimuli rated as less attractive by peers than participants. While the results of Kulcherov and colleagues, 2009, imply role for reward systems in the experience of consensus with group opinion, those of Zaki and colleagues, 2011, suggest that the actual neural representation of value associated with a stimulus converges towards that implied by other people's opinions. Evaluation of attractiveness is relevant to social functioning in general. However, some studies have focused on the interaction between attractiveness and other specific socially relevant signals conveyed by faces. Kemp and colleagues, 2001, showed that attractive faces lead to increased striatal activity when eye gaze is directed straight towards the observer, but not when it is slightly averted. They argue that this difference in gaze direction signals a willingness, versus a reluctance, to engage in social interaction. Some elements of attractiveness evaluation may rely on inferences regarding goals and intentions of the observed face. Making these kinds of judgments about others has been termed theory of mind, and converging evidence implicates brain regions including STS, temporoparietal junction, and medial frontal cortex, MFC, in this complex set of processes. Amadeo and Frith 2006, Frith and Frith 1999, Gallagher and Frith 2003, Sachs and Kenwisher 2003. STS and MFC activation has been observed in fMRI experiments involving attractiveness evaluation, specifically when judgments of attractiveness have explicitly been set as the experimental task. Winston ETAL 2007. Such findings suggest that explicit evaluation of attractiveness may involve complex inferences about the goals and intentions of others, or perhaps self-referential processing. Whether this is the case, and if so, how such processing may interact with assessments of reward value or visual characteristics of attractive faces in the brain, is an intriguing question for future research. 6.4.6 Gender-specific mechanisms of attractiveness evaluation. Several studies have explored whether the neural responses to facial attractiveness are modulated by gender. Increased ACC activity in response to attractive male or female faces and accompanying changes in sympathetic arousal, as indexed by pupil dilation, have been observed in men only. Winston ETAL 2007. Another study found increased medial OFC activity in response to attractive opposite sex faces in men only. Cloutier et al. 2008. Liang and colleagues, 2010, showed nonlinear responses to both attractive and unattractive faces throughout the brain's reward circuitry, striatum, OFC, VTA, as well as linear effects in both medial and lateral OFC. Male participants exhibited stronger nonlinear effects, whereas female participants exhibited stronger linear effects. One study, Krantz and Ishii 2006, has investigated how gender-specific effects of facial attractiveness are modulated by sexual orientation and found stronger activation in the thalamus and neural mechanisms for evaluating the attractiveness of faces. 131 medial OFC specifically for sexually preferred faces. Attentional biases favoring attractive faces are more pronounced in men than in women. Van Hoof et al. 2011. These findings notwithstanding, we would argue that gender differences in the neural processing of attractiveness are surprisingly minor. A number of studies have found only limited gender differences in neural processing of attractiveness. Chatterjee et al. 2009, O'Doherty et al. 2003, and when found, differences have often mainly been down to specific activation patterns for male participants viewing opposite sex faces, which have no direct correlate in women viewing opposite sex faces. For example, in ACC, O'Doherty et al. 2003, Winston et al. 2007. Furthermore, it has been noted that gender-specific differences in processing for opposite sex faces are rather small when compared to the main effects of attractiveness. Winston et al. 2007. Thus, while some gender-specific mechanisms of attractiveness evaluation can undoubtedly be demonstrated, and in particular, male observers seem to exhibit a special engagement of reward mechanisms when they are evaluating attractive opposite sex faces, it appears that non-gender specific ratings on an attractiveness dimension contribute much more strongly to attractiveness evaluation. Such observations argue against conceptualizing attractiveness evaluation chiefly in terms of reward, because the rewarding aspects of facial attractiveness may be expected to be highly gender-specific, although we note there is evidence to suggest that attraction occurs towards physically attractive strangers irrespective of gender, e.g. Verne et al. 1968. Instead, they support an account in which attractiveness is evaluated as a form of beauty. In such a case, one would predict some degree of commonality in the neural mechanisms underpinning evaluation of facial attractiveness and evaluation of other beautiful objects, such as works of art for example. This possibility will be explored in the discussion at section 6.5. 6.4.7 Role of the prefrontal cortex in neural processing of facial attractiveness. Another perspective, which implicates the prefrontal cortex in the processing of attractive faces, can be gained from the study of neural mechanisms of valuation. Attractive faces have both an immediate experience value, i.e. they are intrinsically rewarding, and a more decision-related value, defined as value ascribed to an item to aid decision-making, e.g. in an economic exchange task. Smith et al. 2010. Smith and colleagues, 2010, made use of face stimuli varying in attractiveness and images of banknotes indicating monetary gain or loss. For both stimulus types, they showed that the ventromedial prefrontal cortex, VMPFC, a region known to be important in the representation of decision value, Knudsen et al. 2007, Plasman et al. 2007, could be functionally fractionated, with bold activity and anterior VMPFC being associated with experience value and bold activity and posterior VMPFC being associated with decision value. Importantly, the decision value signals in posterior VMPFC were present even in the absence of an overt choice task. 6.5 discussion. We now set out to integrate and discuss some of the key findings from imaging investigations of the neural mechanisms for evaluating attractiveness in faces, which have been 132 Sposketoff and Joel S. Winston outlined in this chapter. We make comments on possible fruitful future directions in the field, and place particular emphasis on discussing the relevance of this literature to the study of aesthetic preference more generally. 6.5.1 Summary and interpretation of findings from studies of the neural mechanisms for evaluating facial attractiveness. A number of studies have hypothesized that attractive faces are processed by the brain as rewarding stimuli. Findings seem to converge on increased bold fMRI activation in nucleus accumbens, medial OFC, and ACC when viewing attractive faces. Aharon et al. 2001, O'Doherty et al. 2003, Winston et al. 2007. In particular, there is convergent evidence to support a key role for the OFC. The results of several studies highlight a functional fractionation of this region, with medial OFC being responsive to attractive faces, and lateral OFC being responsive to unattractive faces. Cloutier et al. 2008, Hampshire et al. 2012, O'Doherty et al. 2003. Such findings sit well with more general frameworks implicating OFC in representing the effective and motivational value of stimuli, e.g. Rolls 2000. Given the amygdala's responsiveness to both repetitive and aversive stimuli in a number of contexts, there has been a rationale for predicting nonlinear bold responses to attractiveness in this region. Both linear and nonlinear responses to attractiveness have been demonstrated not just in the amygdala and medial OFC, Winston et al. 2007, but also when using highly unattractive disfigured faces at the negatively valenced end of the scale in ACC, lateral OFC, and striatum, Yang et al. 2010. The right amygdala was the region most consistently associated with attractiveness evaluation in two recent meta-analyses, Stock et al. 2010, Mency-Lutsky et al. 2012. The latter of these studies suggested a degree of functional fractionation, with linear bold responses in the ventral amygdala, responds most strongly to negative faces, and nonlinear bold responses, to both ends of the attractiveness dimension, in the dorsal amygdala, Mency-Lutsky et al. 2012. Mency-Lutsky et al. 2012 argue that the ventral portion of the amygdala contributes to processing of valence, whereas the dorsal portion is involved in representing the salience or value of ambiguous facial information. This view dovetails neatly with the work of Wayland and colleagues, 2001, which support the similar functional fractionation of amygdala. Overall, these findings and their interpretation support an important role for the amygdala in facial attractiveness evaluation, consistent with both responding to negatively valenced faces, quite possibly to guide avoidance behavior, and indexing relevance of a particular face in a social context. A handful of other studies have anchored hypotheses regarding the neural evaluation of attractiveness within popular frameworks for neural processing of faces, e.g. Haxby et al. 2000, rather than reward processing systems. Chatterjee and colleagues, 2009, demonstrated increased bold activation in occipitotemporal areas, including FFA and STS, in association with increasing attractiveness of computer-generated faces. In patients with brain lesions resulting in prosopagnosia, urea, and colleagues, 2008, have shown that FFA, and possibly STS, are likely to play a part in processing facial attractiveness, though the data do not go as far as showing that either region is of critical importance. With regard neural mechanisms for evaluating the attractiveness of faces 133 to congenital, rather than acquired prosopagnosia, the evidence suggests that facial attractiveness evaluation is preserved in many, but not all individuals with the condition. Carbon et al. 2010, L. E. Brand et al. 2006, Sadr et al. 2004. Considerable evidence therefore exists to support the hypothesis that regions of the core system for face perception are involved in facial attractiveness evaluation, but there is a lack of clear evidence that any of them are of critical importance. It remains unclear how well evaluation of facial attractiveness fits in with the dual processing streams for invariant and dynamic/social aspects of faces proposed by Haxby and colleagues, 2000. Senior, 2003, presented an extension of the model of Haxby and colleagues, 2000, to include neural processing of facial attractiveness. Particular focus was given to links between dynamic facial processing systems, centered on STS, and a proposed new part of the extended system for face processing, specialized for evaluation of facial attractiveness. Given more recent evidence, it seems likely that both invariant and dynamic streams of the model of Haxby and colleagues, 2000, are involved in attractiveness evaluation. Whether certain aspects of facial attractiveness are processed primarily by the invariant stream and others primarily by the dynamic/social stream remains largely an open question. It is important also to bear in mind that considerable overlap between these two processing streams has been demonstrated. One important distinction to make is between studies that have made attractiveness evaluation task relevant and those that have investigated implicit evaluation of attractiveness, in which case participants are performing an unrelated task to facial attractiveness evaluation whilst viewing faces that vary in attractiveness. Implicit attractiveness evaluation has been shown to engage regions that form part of the reward network including the ventral striatum, Aheron et al. 2001, and OFC, O'Doherty et al. 2003, suggesting that processing of attractive faces as rewards occurs automatically. Winston and colleagues, 2007, specifically addressed the distinction between implicit and explicit processing of facial attractiveness and therefore sought to determine how neural responses are modulated as a function of task, direct evaluation of attractiveness, versus determining the age of faces which also vary in attractiveness. Bilateral STS, bilateral posterior OFC/anterior insula, and medial prefrontal areas, all responded more strongly during explicit attractiveness evaluation, in most cases in a task-dependent rather than stimulus-dependent fashion. The involvement of STS and MFC, regions important for theory of mind functions such as inference about the goals and intentions of others, should prompt future empirical investigation of whether such inferences are necessary for direct and explicit attractiveness evaluation. Uria and colleagues, 2008, found that explicit attractiveness evaluation was correlated with increased fold activation in FFA. On the other hand, a study by Chatterjee and colleagues, 2009, found that ventral occipitotemporal areas were activated during both implicit and explicit attractiveness evaluation, whilst explicit attractiveness evaluation was selectively accompanied by activation in insula and inferior and medial prefrontal regions. Finally, an EEG study, Van Hoof et al. 2011, found that both early and late ERP components related to attractiveness evaluation were present despite such evaluation being implicit. It seems that much of the motivationally relevant processing of attractive faces, as well as much of that pertaining to visual features of the face, in 134 Sposketoff and Joel S. Winston occur automatically, without an observer's explicit attempt to evaluate attractiveness. For a recent review on the topic of automaticity in face perception and social judgment, see Bart et al. 2012. On the other hand, explicit attractiveness evaluation seems to involve activation of regions implicated in more complex processes of social cognition, which play a part in allowing us to infer the goals and intentions of others, or to compare the dispositions and traits of others to those of ourselves. Such explicit evaluation also results in activation of ventral parts of the visual system and prefrontal regions that may support visual awareness. Rees 2007. Two meta-analyses of studies of the neural processes underlying facial attractiveness evaluation have provided largely overlapping results, showing most consistent activation in amygdala, OFC, and striatum. Stock et al. 2010, Menzies-Lutski et al. 2012. A handful of studies have used EEG to study the neural correlates of facial attractiveness evaluation, with findings converging towards the presence of both early and late ERP components of processing, postulated to correspond to attentional orienting and affective/motivational processing respectively. Johnston and Oliver Rodriguez 1997, Van Hoof et al. 2011, Warhide et al. 2007. Two studies have focused specifically on how neural correlates of attractiveness evaluation are modulated by group opinion, finding that activation of the ventral striatum decreases when an individual's opinion conflicts with the group's. Kulcherov et al. 2009, and furthermore, that facial attractiveness-related representations in the ventral striatum and OFC are altered for more prolonged periods, at least 30 minutes, to fit in with group opinion. Zaki et al. 2011. Aside from being modulated by social context, responses to facial attractiveness are affected by other socially relevant facial signals, such as direction of eye gaze. Camp et al. 2001. Reward mechanisms seem to be engaged mostly for opposite-sex faces. Aheron et al. 2001, and more so for male observers. Cloutier et al. 2008. While there may also be other regions activated specifically for sexually preferred faces, Krantz and Ishii 2006, as well as some differences in the linearity/non-linearity of neural response to attractive faces dependent on the gender of the observer. Liang et al. 2010, overall gender invariant effects of attractiveness appear to be more prominent. Winston et al. 2007. A handful of studies have explored other aspects of facial attractiveness processing, including interaction with memory formation systems. Sukaira and Cabeza 2011, and the role of the MPFC in representation of both value and value-based decisions in relation to attractive faces. Smith et al. 2010. In sum, investigations of the neural mechanisms of facial attractiveness evaluation have focused mainly on the role of reward systems in visual processing systems. A number of robust and replicable findings have enabled some key brain regions to be defined, and putative networks to be sketched out. However, a great many important details remain to be clarified. Our understanding of how some of the structural and configural facial determinants of attractiveness are processed in the brain remains limited. Connectivity analyzes to establish how some of the regions involved in attractiveness evaluation interact, as well as experiments to establish the details of interplay between reward systems and visual systems during attractiveness evaluation, are as yet lacking. Some time ago, Senior, 2003, Neural Mechanisms for Evaluating the Attractiveness of Faces 135 has argued that the amygdala is likely to be a key link between reward and visual systems in the evaluation of facial attractiveness. How facial attractiveness evaluation interacts with processing systems for social cognition, memory formation, representation of value, and many other domains of cognitive processing, are also avenues that remain barely explored. 6.5.2 Do mechanisms for processing of facial attractiveness overlap with those for processing of beauty and aesthetic experience. Neuroaesthetics, the term originating from the work of Zeki, 1999, is concerned with the neural mechanisms governing beauty perception in art. In many instances, the scope can be broadened to encompass objects or scenes that would not traditionally be classed as art, but which nevertheless invoke intense, pleasurable feelings in the observer. The study of neuroaesthetics has centered on the visual domain, although the principles are felt to apply equally to other domains, for example music or literature. Chatterjee 2010. Although the definition of aesthetic experience is broad, one can readily argue that both within the realm of visual art, and as part of real-world visual scenes, the human face is often an object that invokes such experience in the observer. Certainly, it seems intuitive that attractive faces would also be aesthetically pleasing, and indeed the two terms have often been used interchangeably in the social and evolutionary biological literature, but ultimately the distinction between these two constructs remains incompletely defined. The neural mechanisms that underlie aesthetic evaluation and experience have come under scrutiny in recent years, and there are a small but growing number of neuroimaging studies aimed at this question. This line of work is tackled in more detail elsewhere in this volume and has previously been discussed in several detailed reviews and commentaries. Selakonda et al. 2011, Chatterjee 2010, Didio and Galiz 2009, Nadal et al. 2008, Ramachandran and Herstein 1999. To what extent does neural processing of facial attractiveness overlap with processes for evaluating beauty and aesthetic value outside the context of faces? The answer to this question would be best facilitated by studies that have made use of both attractive faces and other beautiful stimuli in the same set of experiments. Kawabata and Zeki, 2004, investigated the neural processing associated with assessment of visual beauty irrespective of category of visual stimulus. Whilst undergoing fMRI, participants were asked to rate, in terms of their beauty, paintings depicting portraits, i.e. faces, landscapes, still life scenes, and abstract compositions. Differentiation between beautiful and ugly images across all these categories was tracked by medial OFC activity. More recent work has shown that the degree of activation of the medial OFC correlates with beauty scores given not just to different classes of visual stimuli, but also to stimuli of different modalities, in this case, both visual and auditory stimuli. Ishizu and Zeki 2011. Such findings, converging on medial OFC, have led Zeki and colleagues to propose that this region represents the neural correlate of all beauty. Ishizu and Zeki 2011. Such a proposal places attractiveness evaluation in the OFC in a broad neuroaesthetic context. However, one may consider the role of the OFC even more broadly as a region mediating the rewarding effects of stimuli, be they beautiful or not. This broader view would be supported by 136 Bosgethoff and Joel S. Winston findings that the medial OFC is activated by monetary reward. For example, Elliott et al. 2003, O'Doherty et al. 2001. Another study employing fMRI to determine the neural correlates of aesthetic preference for paintings, Vartanian and Goel 2004, found a correlation between increased aesthetic preference and increased activity in cingulate and occipital cortices, as well as decreased aesthetic preference and decreased activity in right caudate. Again, the reported pattern overlaps with striatal and occipital areas activated during facial attractiveness evaluation. Selakonda and colleagues, 2004, used MEG to investigate the neural correlates of aesthetic preference. Judging stimuli as beautiful was found to correlate with late signal, 401,000 ms, changes over left dorsolateral prefrontal cortex. Nadal and colleagues, 2008, comment on the surprising lack of correlation between aesthetic preference and neural activation in the amygdala in the above studies. One possible reason they suggest for this is that the stimuli used did not extend far enough into the negatively valence end of the aesthetic value dimension. We would suggest that an alternative explanation is that the studies were not specifically designed to look for involvement of the amygdala. Activation in this brain region can be difficult to demonstrate using both fMRI and EEG/MEG, due to artifact from nearby air-filled sinuses, and the region's distance from the brain surface, respectively. In addition, as we have discussed, an important component of the amygdala's response to attractiveness, and potentially to beauty more generally, is nonlinear. Menzigletsky et al. 2012, Winston et al. 2007. By and large, the studies we describe in this section have not specifically looked for nonlinear patterns of neural activation, and this may be an important reason for their lack of demonstrable amygdala activation. One study that shows little concordance between neural networks involved in aesthetic preference and those we have outlined for facial attractiveness evaluation is that of Jacobson and colleagues, 2006. In this fMRI experiment, aesthetic judgments regarding visual stimuli, as compared to symmetry judgments, activated prefrontal, posterior cingulate, left temporal pole, and the temporoparietal junctional regions. Importantly, rather than seeking out regions where activation correlates with degree of beauty ascribed to the stimulus, as undertaken in other studies investigating the neural correlates of aesthetic preference, this study contrasted aesthetic valuations with assessments regarding symmetry. This difference in experimental design may explain disparities between these findings and those of other studies addressing the neural correlates of aesthetic preference, Nadal et al. 2008. In addition, given that we know symmetry is an important determinant of facial attractiveness, Rhodes et al. 1998, as well as of beauty more generally, Enquist and Iraq 1994, it seems likely that symmetry and beauty were confounded in this experiment, making interpretation of the results difficult. While the results from these neuroimaging studies, which sought to clarify the neural mechanisms of aesthetic preference, seem quite diverse, they have recently been synthesized into unified conceptual frameworks, Selakonda et al. 2011, Chatterjee 2010. There appears to be a fair degree of overlap between the findings of fMRI studies of facial attractiveness evaluation and those of aesthetic preference. Findings from EEG also show neural mechanisms for evaluating the attractiveness of faces. 137 such overlap, as reviewed by Nadal and colleagues, 2008. EEG studies of aesthetic preference have led to the emergence of a two-stage processing model with early signal changes, around 300 milliseconds, corresponding to initial impression, and later signal changes, around 600 milliseconds, corresponding to a deeper aesthetic evaluation, Jacobson and Hochul 2003. Such a model bears clear similarity to the two temporal stages of processing described for evaluation of facial attractiveness in section 6.4.4. In sum, there is likely to be considerable overlap between neural processing of aesthetic preference and facial attractiveness, although in most cases this can currently only be inferred from similarities between findings of different studies, and there is a paucity of direct comparison within the same study, with the exception of Kawabata and Ziki 2004. Future studies dedicated to addressing this question would be illuminating. In addition, investigations into the neural processing of facial attractiveness have been guided by highly developed conceptual frameworks that describe neural processing of faces, Bruce and Young 1986, Paxby et al. 2000, and rewarding stimuli, Delgado 2007, and have furthermore begun to generate unique frameworks of their own, e.g. Senior 2003. Such frameworks, besides those already built around understanding aesthetic evaluation, e.g. Chatterjee 2003, could usefully guide further investigation into the neural correlates of aesthetic preference. There is much scope for mutual benefit from continued interaction between these two fields. 6.6 Conclusion. A growing number of experimental studies, making use of neuroimaging methodologies as well as patients with brain lesions, have shown that there is an extended network of brain regions which are involved in evaluation of the attractiveness of faces. Attractiveness modulates threefold activity in regions important for visual processing, including those specialized for face processing, e.g. FFA, and for processing of social signals from faces as well as other sources. Frequently, attractive, as well as unattractive, faces undergo processing within the brain's reward centers in the OFC and striatum. In addition, the amygdala plays an important role in indexing the social relevance of stimuli in the external environment, and in line with this, appears consistently to be involved in evaluation of attractiveness, a trait that carries important social implications. Some dissociation has been shown between regions activated during implicit attractiveness evaluation, and those activated during explicit evaluation. In particular, explicit attractiveness evaluation engages medial frontal and superior temporal regions which may reflect theory of mind or self-referential evaluations relevant to adapting attitudes and behavior in social contexts. A number of the neurobiological findings, not least the considerable involvement of reward systems, are potentially in keeping with the fundamentally important role of attractiveness evaluation in terms of reproduction and survival. In addition, there is growing evidence that some of the neural mechanisms for processing of facial attractiveness may be common to processing of beauty more generally, and thus the study of the neurobiology of facial attractiveness is of particular relevance to the study of neuroaesthetics. A great many questions remain open in this field, and we envisage substantial further development in coming years. Chapter 7 Indeterminate Artworks in the Human Brain. Robert C. Pepperell and Alumet Ishai 7.1 Visual Indeterminacy and Art History. This chapter summarizes previously published work by the authors on the topic of visual indeterminacy. Pepperell 2006, Ishai et al. 2007, Fairhall and Ishai 2008, Pepperell 2011. Visual indeterminacy occurs when an image or a scene is structured in such a way as to defy immediate or easy recognition. Artists have long been fascinated by indeterminate images and have frequently exploited their capacity to perplex audiences. In the first major study of unrecognizable images in art history, Gamboni, 2002, surveyed the occurrence of visual indeterminacy in works stretching deep into art history. He showed how artists have in various ways deliberately included elements or passages within paintings that confounded the viewer's capacity to identify what they saw. He cites, for example, the work of the symbolist artist Odilon Redon, who produced a series of drawings in pastels in the late 19th and early 20th century that are full of richly suggestive forms often lacking clearly definable objects. A major piece, Roger and Angelica of 1910, Museum of Modern Art, New York, Lily P. Bliss Collection, depicts just recognizable figures in a misty landscape of loosely depicted water and rocks. In his Confessions of an Artist, Redon was explicit about his purpose. The title that occasionally defines my drawings can be superfluous. It is justified only when it is vague, indeterminate, and even equivocal. My drawings inspire and cannot be defined. They do not determine anything. They place us, as music does, in the world of the ambiguous and the indeterminate. Endora 1995, p. 55. One artist who exploited the phenomenon of visual indeterminacy perhaps more than any other was J.M.W. Turner, the most renowned and influential British painter in modern times, who was widely famed for his atmospheric landscapes and seascapes. Like many artists, Turner's reputation ebbed and flowed throughout his long career. Given how he is regarded now, it can be surprising to learn how poorly his works were received by the public and influential critics during his lifetime. Even some of his early works, which we would now judge to be quite clear and precise, were seen by many contemporaries as foggy, indistinct, and unreadable. Yet despite contemporary hostility to his work, Turner's work was to have a profound effect on the future course of art, especially on a generation of young French artists who had taken refuge in London during the Franco-Prussian War in the 1870s. Prominent among them was Claude Monet, who saw many of Turner's 144 Robert C. Pepperell and Allumette Ishii paintings during his sojourn, House 1986, p. 113. Monet was to find in Turner the kind of expressive freedom to evoke natural atmospheres that led in 1872 to the painting Impression, Sunrise, Musée Marmottan Monet, Paris, the title of which, when exhibited in 1874, gave the Impressionist movement its name. This loose and fluid sketch of the misty sun above a harbor in El Havre famously provoked a bemused critic to ask, what does that canvas depict? Leroy 1874. Many artists of Monet's generation were profoundly influenced by contemporary theories of perception, such as those proposed by Hermann von Helmholtz, which stressed the way we infer properties of the world from raw sensory data. In the case of vision, as artists then believed, this raw sensation consisted of patches of color detected by the retina which were then interpreted as objects by the higher brain. In his seminal book Art and Illusion, Gombrich, 1960, p. 161, referred to this inferential process as the beholder's share of the pictorial bargain, this being a part of the meaning generated by the viewer from his or her own cognitive resources. In a famous passage quoted by Gombrich, 1960, p. 250, the art critic and champion of Turner, John Ruskin, advised painters to be guided only by what arrives at the childish or innocent eye, and to record only flat stains of color, merely as such, without consciousness of what they signify as a blind man would see them if suddenly gifted with sight. This was an approach Monet himself sympathized with, leading him to remark that he wished he had been born blind and then suddenly gained his sight so that he could have begun to paint in this way without knowing what the objects were that he saw before him. Nochlin 1966, pages 35-6. Thus for Monet, the function of painting was not to obscure but to faithfully depict the appearance of the world. This was to be achieved by recording what he saw, and the way he saw, rather than what he knew from prior knowledge or experience to be in front of him. Take, for example, one of the 30 or so paintings he made of Rouen Cathedral during the 1890s, which captured the appearance of the building's facade in a variety of lighting and weather conditions. These paintings were intended to be less depictions of a particular building and rather the experience of the light reflected by the building. House 1986, p. 221. Vasily Kandinsky, who is often credited as the originator of abstraction, was profoundly affected by seeing one of Monet's series of paintings depicting haystacks when they were exhibited in Moscow in 1895. Kandinsky was struck by the fact that he could clearly see the painting in front of him but not what it represented. He later recounted, and suddenly for the first time I saw a picture. That it was a haystack, or rather, a grain stack, the catalogue informed me. I did not recognize it. And I noticed with surprise and confusion that the picture not only gripped me, but impressed itself ineradicably upon my memory. Painting took on a fairy tale power and splendor. And, albeit unconsciously, objects were discredited as an essential element within the picture. Parsons and Gale 1992, p. 255. Kandinsky later recalled another similar experience which occurred when he returned to his studio at dusk and was astonished to see an indescribably beautiful picture, pervaded by an inner glow standing against the wall. Lindsay and Virgo 1982, pages 369-70. In it he could discern only forms and colors and no comprehensible objects. He then indeterminate artworks and the human brain 145 realized it was one of his own paintings turned on its side, but he had simply failed to recognize the subject. This experience, compounded by the one he had in front of the Monet, was to lead Kandinsky directly to develop a new form of non-objective art. It was form of art that was not purely abstract, as later critics often claimed it to be, but rather indeterminate in the sense that objects were suggested in a book but never explicitly rendered. Gerhard Richter is a contemporary German artist working in a number of distinct styles which include both highly rendered photographic-like paintings as well as large-scale expressive pieces produced by spreading and scratching wet paint with huge squeegees. It would be too simplistic to describe either style as straightforwardly realistic or abstract, although these labels are often used. Listening to Richter's own statements it becomes clear that his work is better described as indeterminate. In many of his images Richter's aim is to create sense of mystery or uncertainty about what is being depicted or represented. In the painting Alps 2, 1968, MKM Museum Kupfersmole for Modern Kunst, Duisburg, Germany, Sylvia, and Ulrich Strobel collection, for example, we are presented with a seemingly abstract mass of gray, formless brush marks. Only through considerable effort can we make out what appears to be a snowy mountain range. Richter says, pictures which are interpretable, and which contain a meaning, are bad pictures. A good picture, on the other hand, demonstrates the endless multiplicity of aspects. It takes away our certainty, because it deprives a thing of its meaning and its name. It shows us the thing in all the manifold significance and infinite variety that preclude the emergence of any single meaning or view. Elber and Oberst 2009, pages 32-3. This brief survey of art and visual indeterminacy demonstrates, first, that artists have understood and tried to exploit the perceptual effects produced by non-specific images. Secondly, it shows that artists, in order to use these effects best, have acted scientifically, exploring the nature of visual perception through their artistic practice. Finally, it shows that visual indeterminacy, far from being a tactic on the part of artists to confound their public audiences, is understood by them to be a potential source of profound aesthetic experience. Robert Pepperell is a contemporary artist who has a long-standing interest in visual indeterminacy. Over many years he has sought to construct images that are truly indeterminate in that they finally balance recognizability and abstraction. In this way they excite the inquisitiveness of the viewer's visual system while frustrating its capacity for recognition. After a long period of experimentation, with many false starts, Pepperell gradually developed a method of drawing and painting which seemed to produce this effect consistently. Figure 7.1. Many of his paintings use a classical pictorial architecture of the kind frequently found in European paintings made between the 1500s and early 1900s, which incites a strong expectation that the painting will contain a recognizable scene since paintings of this style and period are strongly associated with immediately recognizable content. By using this overall pictorial structure but organizing the content in such a way that no objects could be deciphered as objects, Pepperell was able to achieve consistently indeterminate pictorial effect, for the artist's personal perspective. See Pepperell 2006 and 2011. 146 Robert C. Pepperell and Allumette Ishii 7.2 Scientific background to visual indeterminacy. Visual indeterminacy is related to, but not to be confused with, the phenomenon of ambiguous or reversible images. The Necker cube, a wireframe cube that can be interpreted in two mutually inconsistent ways, the duck-rabbit illusion, in which a single image is perceived to be either a duck or a rabbit, or the boring vase image, in which the outline of a vase can be also seen as two faces in profile, are all open to alternating interpretations, and in each case the alternative meanings are quite determinate. Kleinschmidt et al. 1998, Meng and Tong 2004. Similarly, so-called hidden figures, such as the case of the Dalmatian dog in R.C. James' famous photograph, Gregory 1970, Palmer 1999, Ramachandran and Herstein 1999, depend on our capacity to find meaningful objects in ambiguous stimuli. However, neither ambiguous nor hidden images are visually indeterminate, in the sense being used here, since what distinguishes indeterminate stimuli is their resistance to final identification of any kind. An analogy can be drawn between visual indeterminacy and the rare neurological disorder of associative visual agnosia, a widely known case study published by Humphreys in Figure 7.1 Territory by Robert Pepperell. In this example of indeterminate painting, natural forms are implied while at the same time resisting easy or immediate identification. Indeterminate artworks in the human brain 147 Rudosh, 1987, concerned a patient, John, who had suffered a stroke resulting in a bilateral lesion in the region supplied by the posterior cerebral artery. Much of John's visual system was spared, but his ability to recognize what he saw was greatly impaired. When shown a series of line drawings of everyday objects he was able to identify only a small proportion, and relied on working out what was depicted from specific clues within the image, such as the curliness of a pig's tail, rather than by seeing the object as a whole. P60. Humphreys and Rideau excluded other possible factors that could have contributed to John's inability to recognize everyday objects when arriving at their diagnosis of associative visual agnosia, including any residual deficit in his stored knowledge or visual sensation. He could still readily identify objects by touch, by describing them from memory, and could copy line drawings of objects, albeit laboriously, even when he had no idea what the object was. V69. Humphreys and Rideau argue that John's case provides evidence to support the idea that visual perception occurs through at least two distinct sets of processes, pages 1012. The first process is organize the perceptual input data according to position and orientation, and bind multiple visual elements into wholes. A subsequent set of processes match that input data to associations about function and meaning. The authors conclude, in general terms, John's case supports the view that perceptual and recognition processes are separable. P104. In another important study of visual agnosia, Farah, 2004, concurs with Humphreys and Rideau's distinction between perceptual input and the conceptual associations involved in visual object recognition. Visual form agnosia validates the distinction implicit in the labels early and intermediate vision, on the one hand, and high-level, object vision on the other, by showing the first set of processes can continue to function when the second set is all but obliterated. It shows us a kind of richly elaborated but formless visual stuff, from which things can be derived. P156. The phrase richly elaborated but formless visual stuff is an apt description of the appearance of the world at the moment of visual indeterminacy, resulting from the failure to correlate this visual stuff to the bank of stored memories and associations. This can occur to us all occasionally, especially when presented with indeterminate images, but for the unfortunate sufferers of visual agnosia it is a permanent condition. There is some evidence from neuroscientific studies that the perception of indeterminate stimuli brings about measurable changes in brain activity. An EEG study by Sup and colleagues, 2005, for example, looked at the changes in cortical networks within the time window of the event-related potential component N400. Subjects were shown sequences of grayscale pictures that were more or less recognizable although comparable in terms of size, complexity, and structure. During the viewing of unrecognizable pictures, when compared with recognizable ones, there was a marked increase in cooperation in certain parts of the brain and a greater degree of overall coherence between different regions. The researchers concluded that these changes in brain activity reflected the greater demands made on the viewer's perceptual and cognitive resources and consequent unease involved in the task of semantically matching the undecipherable stimuli. The greater number of coherent increases for meaningless object processing suggests enhanced 148 Robert C. Pepperell and Aluminid Ishai recruitment of more distributed left and right areas during unsuccessful memory search. P1143. Rayner and colleagues, 2004, studied the responses of monkeys to recognizable and unrecognizable images by measuring neural activity in area before on exposure to images that were increasingly degraded, from clear to abstract noise. The monkeys learned to recognize familiar images that were degraded compared to novel ones that were treated in the same way. The researchers found that monkeys exposed to indeterminate images showed significantly increased neural activity in both primary and higher cortical areas of the brain than when faced with familiar or recognizable stimuli. Rayner and colleagues concluded that not only are particular loci in the brain recruited in response to indeterminate stimuli, but that the attempt to decipher such stimuli leads to enhanced overall coordination in brain activity. This suggests that P4 plays a key role in resolving indeterminate visual inputs by coordinated interaction between bottom-up and top-down processing streams. P275. 7.3 Scientific experiments on visual indeterminacy. 7.3.1 Behavioral studies. We, Pepperell and Ishai, met at the Max Planck Institute for Biological Cybernetics in Tübingen, and based on mutual interests in art perception, we decided to study together the neural correlates of viewing at indeterminate paintings. To test the effects of visual indeterminacy, we gathered a set of images that included a selection of Robert Pepperell's indeterminate paintings as well as paintings that were similar in visual appearance to Pepperell's but full of readily identifiable objects. These consisted of works by classical artists such as Turner, Tintoretto, Rubens, Michelangelo, and Fuseli. Examples can be seen at. The paintings were divided into two sets, one grayscale and one color, in order to determine whether there was any significant effect between these conditions. Then the subjects were presented with a number of tasks. They were asked first to indicate whether each image contained familiar objects, and secondly they were asked to rate how powerfully the images affected them. On the basis of informal observations made on viewers looking at Pepperell's paintings in the studio and galleries, we hypothesized that compared with paintings depicting meaningful content, object recognition in indeterminate images would take longer. We were also interested in the extent to which aesthetic affect depends on how easily objects in the images could be recognized. The results showed that it took subjects significantly longer to respond to Pepperell's indeterminate images, and they reported seeing objects in them 24% of the time. It is interesting that subjects were significantly slower in making judgments about indeterminate paintings compared to the determinate ones, and this was true whether or not they recognized familiar objects. Ishai et al. 2007. The findings suggest that when subjects are presented with the problem of resolving indeterminate stimuli, a greater degree of cognitive processing is required than would be the case when confronted with immediately indeterminate artworks in the human brain. 149 recognizable images. Importantly, we found a significant degree of correlation between the amount of time it took subjects to identify objects and the extent to which they rated them as aesthetically effective. Figure 7.2. Somewhat contrary to expectations, we found that all the images were given very similar aesthetic ratings, whether they were recognizable or not. Previous studies have tended to indicate that subjects with little or no expert art knowledge prefer figurative more than abstract art. Healy and Enns 2002, Vartanian and Goel 2004. These results suggest that in forming their judgment, subjects were less influenced by the semantic content than the overall visual structure of the image. In art historical terms, visual structure would be referred to in terms of the formal properties of the work, that is, the shape, color, and texture of an artwork as opposed to its content, which consists in the meaning, narrative, or objects it depicts. There has been a long-standing debate among art theorists as to which of these properties is the most important in defining the aesthetic value of a work of art. Bell 1914. On the basis of the results we obtained, it would seem that the recognizable content of images is less important in affecting aesthetic evaluation than overall visual appearance. It is worth noting that we used a somewhat unusual method of measuring aesthetic affect. Non-art specialists often conceive of art in terms of its capacity to evoke feelings of beauty, tranquility, balance, harmony, or order. It is not uncommon to find this assumption held among those in the scientific community wishing to measure the psychological impact of art. Yet art history shows that while many artworks can indeed be described in terms of beauty, harmony, pleasure, and the like, there are many highly important artworks that could be better described as ugly, disturbing, violent, or garish. Take for example Grunewald's Isenheim altarpiece, c.1512, Unterlinden Museum, Colmar, France, which shows an emaciated Christ writhing in agony on the cross, or the grotesque fleshy distortions of Dali's soft construction with boiled beams, 1936, Philadelphia Museum of Art. Figure 7.2 Effects of aesthetic judgments on object recognition and memory retrieval. Reaction time during the object recognition task predicted subsequent aesthetic affect rating. Longer reaction times in the object recognition task were later associated with stronger affect ratings. Right, aesthetic judgment predicted recognition memory. The stronger the affect rating of an image was, the more likely this painting was to be remembered a week later in a surprise memory test. VA, representational paintings by various artists. RP, indeterminate paintings by Robert Pepperell. 3000 VA, object, RP, no object, reaction time, MS, 2500, 2000, 1500, 1500, 0, none little Fairberry VA, RP percent of recognized old paintings, 180, 60, 40, 0, 20, none little Fairberry, A, B, 150 Robert C. Pepperell and Aluminid Ishai, Philadelphia, PA. Such images can have immense power, yet could hardly be described as visually pleasant. We found, therefore, that measuring the potency of an artwork would be less constraining than merely measuring its beauty. Thus we asked subjects to base their aesthetic rating on how powerfully the image affected them on a scale from 1 to 4. The correlation between response latency and heightened power rating suggests that the perceptual struggle to resolve indistinct objects has some aesthetic value. To test whether memory recall of paintings depends on meaningful content and aesthetic judgment, half the subjects returned for a surprise memory test 8 days after participating in the object recognition and aesthetic judgment experiment. The memory test revealed that more representational than indeterminate paintings were remembered, and that effective strength increased the probability of subsequent recall. Figure 7.2, suggesting that meaningful content is critical for incidental memory. ISHIETAL 2007. The lower memory recall for the indeterminate paintings could be due to their lack of meaningful content. An alternative, but not exclusive explanation, is that it was difficult to remember the indeterminate paintings because they had no prior associations to representations stored in memory. Interestingly, we found significant increase in false alarms for indeterminate compared to determinate paintings. Subjects mistook significantly more new indeterminate paintings as old ones, presumably due to their high degree of visual similarity, or because they recognized Pepperell's unique style. Consistently, our studies with portraits, landscapes, and abstract compositions have shown that subjects falsely recognized new paintings as old ones when the new paintings were visually similar to old prototypes that the subjects previously memorized. Diego and Ishii 2006, Wiesman and Ishii 2008. Taken collectively, the results of our behavioral study suggest that perception and memory of art depend on semantic aspects, whereas aesthetic affect depends on formal visual features. The longer latencies associated with indeterminate paintings reflect the underlying cognitive processes that mediate object resolution. Indeterminate artworks therefore comprise a rich set of stimuli with which the neural correlates of visual perception can be investigated. ISHIETAL 2007. 7.3.2 Functional brain imaging studies. We then conducted an fMRI study, in which subjects performed an object recognition task on 4 classes of paintings: representational, which explicitly depict complex scenes with familiar objects, people, animals, landscapes, still life; indeterminate, in which familiar objects are only suggested; abstract, which do not depict any familiar objects; and scrambled images. Figure 7.3. We hypothesized that subjects would rapidly recognize familiar objects depicted in representational paintings, but would be slower to report the presence or absence of recognizable objects in abstract and indeterminate paintings. Moreover, we predicted a posterior to anterior gradient of activation along the ventral visual pathway, such that with increased recognition of familiar content in the paintings, differential activation would be observed in more anterior, higher tier, object-selective areas. Finally, we postulated that indeterminate paintings would invoke visual imagery-related activation in parietal and prefrontal cortices. Indeterminate artworks in the human brain. 151 replicating our behavioral study, subjects reported seeing familiar objects in 36% of the indeterminate paintings, and in 18% of the abstract paintings, although these images lack object-suggestive content. Moreover, subjects rapidly recognized familiar objects in representational paintings but showed longer reaction times to indeterminate and abstract images. Fairhall and Ishii 2008. These differential response latencies suggest, again, an automatic recognition of objects when they were explicitly depicted, but required more effortful cognitive processes such as visual search, when the objects were ambiguous or suggestive. All paintings evoked activation within a distributed cortical network that included regions in the visual cortex, as well as parietal, limbic, and prefrontal regions. Figure 7.3. Consistent with our hypotheses, representational paintings with meaningful content evoke stronger activation than abstract and indeterminate paintings in the fusiform gyrus, a region that responds to assorted common objects, including faces, houses, animals, and tools. Chao ETAL 1999, ISHIETAL 1999, ISHIETAL 2000B, Hack ETAL 3.65, 1.732.710, 3.66. All paintings scrambled representational, indeterminate scrambled, indeterminate abstract, indeterminate representational. Indeterminate abstract scrambled, A, B. Figure 7.3. Viewing paintings as compared with scrambled pictures elicits activation in a distributed network of visual, limbic, parietal, and frontal regions. Comparing representational with indeterminate paintings revealed activation in the temporoparietal junction, a region that mediates the allocation of spatial attention across visual scenes. Comparing scrambled pictures with indeterminate paintings and abstract paintings with indeterminate ones reveals activation in the precuneus and medial frontal gyrus, regions that mediate the generation and maintenance of mental images from long-term memory. 152 Robert C. Pepperell and Alumet Ishii 2001. These results are consistent with a study in which enhanced activation in the fusiform gyrus was observed when representational paintings were compared with filtered paintings, namely representational and abstract paintings that were subjected to a median noise filter, which created random distribution of color levels. Vartanian and Goel 2004. The indeterminate paintings, when compared with the representational and the abstract compositions, evoke less activation in the right hippocampus. Fairhall and Ishii 2008. This reduced activation may reflect the poor encoding of the indeterminate paintings, consistent with our behavioral study, in which subjects recalled significantly fewer indeterminate than representational paintings in a surprise memory task. ISHIETAL 2007. To identify the neural correlates of object indeterminacy further, we compared activation evoked by scrambled paintings with activation evoked by the indeterminate paintings. We found that the scrambled paintings evoked enhanced activation in the precuneus and the medial frontal gyrus, regions of the imagery network that mediate the generation and maintenance of mental images from long-term memory. Miyashita and Chong 1988, Fletcher ETAL 1995, Meckel ETAL 2004, ISHIETAL 2008, ISHIETAL 2002. Post-scanning debriefing revealed that most subjects used mental imagery during the perception of the scrambled paintings in order to decide whether the images contained any familiar objects. In contrast, to decide whether the indeterminate paintings, which were rich with suggestive objects, contained any recognizable objects, subjects relied on visual similarity and visual associations. A direct comparison of representational and indeterminate artworks revealed significant activation in the temporoparietal junction, TPJ, a region that has been implicated in exerting attentional control over switches from local to global processing, Think ETAL 1996, and the allocation of spatial attention across the visual scene, Corbett ETAL 2005. The enhanced activation within the TPJ for representational paintings reflects the binding of object form and spatial location within these cluttered visual scenes. Thus, the recognition of meaningful, familiar content in artworks is mediated by activation in the TPJ. Incidentally, in another study, the left, but not the right, TPJ was also activated by paintings that subjects rated beautiful rather than neutral, Kawabata and Seki 2004. In sum, the fMRI study shows that perception of art compositions evokes activation in multiple visual regions, the hippocampus, intraparietal sulcus, and inferior frontal gyrus. Content-related modulation in the fusiform gyrus reflects object perception, whereas hippocampal activation reflects memory consolidation. Imagery-related activation was observed for scrambled paintings. Finally, interpreting composite scenes relies on higher-order associations in the TPJ, which links the various elements of the visual scene, Fairhall and Ishii 2008. It therefore seems that the human brain is a compulsive object viewer, which automatically segments indeterminate visual input into coherent images. To resolve the visual indeterminacy, higher cognitive functions, such as attention, visual imagery, and memory retrieval, are recruited. Indeterminate artworks in the human brain. 153 7.4 Object recognition in Cubist paintings to the naive observer. Cubist paintings contain geometrical forms in which familiar objects are barely recognizable, even in the presence of a meaningful title. In Cubist artworks, objects are broken up, analyzed, and reassembled to produce abstracted forms, which often depict the same objects from different viewing points. We conducted a new fMRI study to test the extent to which a short training session about Cubism would facilitate object recognition in paintings by Picasso, Braque, and Briss all painted in the period before the First World War. Paintings of this period are characterized as being highly indeterminate. They are directly observed depictions of everyday objects, e.g. tables, fruit, newspapers, glasses, but represented in a fragmented manner that makes immediate identification very difficult. Samples of the stimuli can be seen at Art experts, and others familiar with the genre, are able to read these cubist scenes and find within them the various forms and objects from which they are constructed. Those without this expertise tend to see only patterns, lines, and textures rather than distinct objects of any kind. Golding 1988. We hypothesized that subjects who receive training would recognize familiar objects faster than control subjects, and would exhibit stronger activation in object-responsive and attention-related regions. Our subjects, students from the University of Zurich, had no formal art education and reported visiting art museums once a year or less. A meaningful title or the word untitled appeared before each cubist painting, and subjects had to answer the question, do you recognize any familiar objects? By pressing one of two buttons, yes/no, then answer the question, how many objects did you recognize? By pressing one of four buttons to indicate 0, 1, 2, or 3, or more objects. 30 minutes before scanning, half the subjects received a short training session, during which they were presented with information about cubism, viewed examples of cubist paintings, and practiced recognizing familiar objects in these paintings. Relative to the control group, trained subjects recognized significantly more objects in the paintings, and their response latencies were significantly shorter. Moreover, trained subjects took longer to report not recognizing any familiar objects in the paintings. Cubist paintings evoked activation in a distributed cortical network that included extrastriate, parietal, and prefrontal regions. Within the parahippocampal cortex, trained subjects showed a significantly larger spatial extent of activation and a parametric increase in the amplitude of the fMRI signal as a function of the number of objects they recognized. We also found that in trained subjects, the longer response latencies associated with failing to recognize familiar objects were correlated with activation in the frontoparietal network that mediates spatial attention. Wiesman and Ishii 2010. The most surprising and intriguing finding in our study is the enhanced activation in the parahippocampal cortex of trained subjects, the amplitude of which increased as a function of the number of objects recognized. This suggested that the subjects had used broader contextual associations to identify the objects in the paintings rather than the cognitive resources normally linked more specifically to object recognition. The parahippocampal 154 Robert C. Pepperell and Alumet Ishii cortex, implicated in the representation and processing of spatial navigation information, Epstein and Ken Wisher 1998, episodic memory, Gabriele et al. 1997, and remote spatial memories, Spears and McGuire 2007, is a major node in the cortical network for contextual associations, Barr et al. 2008. Associations are formed over time, when repeated patterns and statistical regularities are extracted from the environment and stored in memory. It has been recently suggested that the role of associations is to generate predictions about the immediate future in order to guide behavior, Barr 2007. It is highly likely that due to the short training session, our subjects used contextual associations to perform the tasks. Importantly, our findings provide empirical evidence for Bayesian analysis, which was proposed as a model for object perception, Kirsten et al. 2004, and evoked cortical responses, Friston et al. 2003, Friston 2005. According to the Bayes perspective, the short training session enabled our subjects to match the indeterminate visual input with their top-down predictions. It is reasonable to assume that trained subjects were more likely than control subjects to suppress errors and establish a consensus between the actual bottom-up input and the top-down prediction. Thus, minimizing prediction error resulted in faster recognition of more familiar objects in cubist paintings. The extent to which titles do or should influence the perception of meaning and the aesthetic impression of art compositions is contentious. In art theoretical terms, critics of a formalist persuasion claim that titles are merely identification tags that should not affect the viewer's reading of the work. Others, however, claim titles function as guides to interpretation and provide important contextual cues to engage the attention of the viewer. Gombrich 1960, Fisher 1984. Empirical evidence suggests that titles influence both the understanding and the appreciation of paintings. Letter et al. 2006. In a compelling example of the top-down effects of titles on art perception, viewers' descriptions of the content of paintings varied according to the title, e.g. Agony vs. Carnival, they were offered. Franklin et al. 1993. In our experiment, cubist paintings were preceded by their meaningful title or by the word untitled. We found that meaningful titles facilitated object recognition, but only in trained subjects. Thus, relative to control subjects, trained subjects reported recognizing more familiar objects in paintings with meaningful titles. These findings suggest that meaningful titles can provide the top-down solution for ambiguous visual input, but only when prior knowledge or experience exists. Taken together, these observations suggest that recognition of familiar content in artworks is a skill acquired through training. It is also tempting to wonder whether subjects thus trained in recognizing objects in cubist paintings are also then better at other object recognition tasks. In sum, our studies suggest that the human brain is not a passive viewer of works of art, but a dynamic interpreter that constantly generates predictions about the content and its meaning based on previous encounters with similar visual input. This is especially evident in the case of indeterminate stimuli that force the subjects to adopt different viewing strategies from more conventionally recognizable images. Understanding the content of modern paintings, which are often difficult to read or recognize, is an acquired, context-dependent skill. It is perhaps not surprising that our emotional response to works of art is also influenced by knowledge and context, as suggested by recent studies in Indeterminate Artworks and the Human Brain 155 of Aesthetic Judgment of Paintings, Kirk et al. 2009. If indeed art evolved as a medium for communication by symbols, it seems that with time, as these non-linguistic symbols became more and more detached from their reference, the human brain has accrued additional cortical resources to comprehend their meaning. 8.1 Neural Aesthetic Valuation. In this chapter we concentrate on the respective roles of the ventromedial prefrontal cortex, VMPFC, and the dorsolateral prefrontal cortex, DLPFC, during aesthetic evaluation, particularly the aesthetic evaluation of visual works of art. Activation of these areas has been shown to be modulated by external contextual pressures on viewing, Kirk 2008, Kirk et al. 2009a, Kirk et al. 2011. We also discuss the roles of ACC, hippocampal, and striatal connections in the process of rating and evaluating works of visual art. One way of considering aesthetic experience is through the examination of the neural correlates of sensory and motor responses works of art into other visual images. Much attention has already been devoted to the neural substrate of embodied responses to works of art, and to visual images more generally. Freeberg 1989, Freeberg and Galeese 2007, see also Estate et al. 2004, and Downing et al. 2006 on responses in extrastriate body area, EBA, and DeGelder 2006 on emotional body language, EBL. The role of mirror neurons in the felt simulation of action and implied action has played a central role in these discussions. Rizzolatti et al. 1996, Rizzolatti et al. 2001, Freeberg and Galeese 2007, Didio et al. 2007. Since such accounts, and all accounts of common coding and shared representation, Prince 1997, DeCity and Somerville 2003, emphasize not only perception and action coupling but also the links between sensory and motor responses. Mirror activations in motor and premotor cortices, as well as in the somatosensory cortices, have been examined at some length. For the visual perception of touch in art, see Kaisers et al. 2004, Freeberg and Galeese 2007. For motor responses to art, see also Calvo. Marino 2005, Battaglia et al. 2011. Felt simulatory responses to visual images have become a staple of studies of embodied simulation as well as of empathic responses to images. Galeese et al. 2004, Freeberg 2007, 2009. These have provided a neural account for the kinds of embodied and motor responses to paintings and sculptures described in the work of the French phenomenologist Maurice Merleau-Ponty and his predecessors, including the pioneers of empathy theory, such as Robert Fisher and Theodore Lips, for whom the contextual bias and insulation against bias during aesthetic rating 159 notion of I'm feeling was a fundamental aspect of aesthetic response, e.g. Merleau-Ponty 1945, Fisher 1873, Lips 1903a, 1903b. The connection between movement and emotion as described by Henry James has had a significant revival in the work of Antonio Damasio and others, James 1890, Damasio 1994. The trend towards linking bodily and emotional responses has led to a slew of analyses of the role of amygdala. Ledoux 1992, 1996, Adolphe CTAL 1995, Adolph's 1999, and insular activations and responses to artistic representation, Didio ETAL 2007, for earlier studies of emotional responses to images. See also the very many studies by Lane and Lang, including Lane 1997, Lang ETAL 1993, as well as the wide range of material currently available for the relationship between feelings of disgust and activation of anterior insula. We are now in possession of abundant research on the neural substrates underlying both sensory and affective engagement with works of art, e.g. Friedberg and Gillies 2007. A considerable amount of attention has been paid to the ways in which motor simulation, or a sense of motor simulation of action and movement scene, evokes emotions in the viewer that accord with those intended by the artist, Friedberg 2007. More recently, attention has also been paid to the movements implied by the marks, in other words the traces of the painter's or sculptor's hand on a painting or sculpture, thus expanding the notion of simulation well beyond figurative art to more abstract forms, and to calligraphy as well, Domel to ETAL 2012. Little of this research, however, provides access to the question of aesthetic preference and rating, and even less to understanding the neural correlates of contextual influences on such ratings. While responses in the domain of perception-action coupling provide useful and important evidence of the role of somatic and emotional responses in viewers' engagement with works of art, the degree to which they form the basis of evaluation, ranking, and even judgment is moot. Recent economic and decision-making theory suggests a number of possibilities for the understanding of the neural substrate underlying a subjective evaluation of works of art, of the impact of context on hedonic value, of the varieties of insulation against such contextual influences, and of the impact of domain expertise on such insulation. Montague and Burns 2002. Here we set out the role of prefrontal interactions, most notably between DMPFC and DLPFC in the processes of evaluation, and the relationship between expert and non-expert responses. A number of behavioral studies have shown how information such as titles, labels, texts, and other forms of cognitive supplementation can affect the evaluation of a work of art, e.g. Kupchak ETAL 2009, Letter ETAL 2004, Russell 2003, Kirk ETAL 2008. The neural correlates of aesthetic evaluation began to become clearer with the examination of responses to musical, Blood and Zader 2001, Baumgarten 1986/1750, and pictorial stimuli, Selkonda ETAL 2004. Subjective pleasantness ratings of musical sequences have been shown to correlate with activity in the striatum, amygdala, parahippocampal gyrus, insula, orbitofrontal cortex, OFC, and anterior cingulate cortex, ACC, Blood and Zader 2001, Brown ETAL 2004, Menon and Levin 2005, Kolsch ETAL 2006. Similar findings were reported in two studies using paintings as stimuli, where subjective appreciation of works recruited the CODATE, ACC, and OFC, Kawabata and Ziki 2004, Vartanian and Goel 2004, Kirk ETAL 2008. In a study comparing the networks recruited during aesthetic rating 160, Ulrich Kurt and David Friedberg as compared to symmetry judgments, Jacobson and colleagues found enhanced activity in frontomedian cortex, lateral OFC, inferior frontal gyrus, posterior cingulate, temporal pole, and temporal parietal junction, Jacobson ETAL 2006. Each of these studies provided significant clues to components of the neural networks underlying aesthetic rating. Kawabata and Zikis, 2004, breakdown of the elements of appreciation into comparatives, determined by rigorous analysis of behavioral ratings, produced a set of suggestive, if not conclusive, results. When stimuli rated as beautiful versus neutral were compared, activity in medial orbitofrontal cortex, OFC, ACC, and left parietal cortex correlated with such ratings. When stimuli rated as ugly versus beautiful were contrasted, primary motor cortex was activated. When ugly versus neutral stimuli were compared, no activation was observed. In the case of the rating of beautiful versus ugly, medial OFC seemed to be elevated. Kawabata and Ziki 2004. While the sample size here was small and rather vaguely defined, 5 male and 5 female students with no special experience in painting or art theory, the finding of activity in medial OFC during aesthetic evaluation of beautiful paintings, as rated by subjects, was suggestive enough to use as a base for further experiments that merge with findings from the area of decision-making. Early on, Damasio and colleagues had shown that lesions in medial OFC/VMPFC often lead to decision-making deficits. Becerra ETAL 2000, Damasio 1994. The role of VMPFC in emotional appraisal, as in the case of valuation of emotional valence of facial expressions, e.g. Aharon ETAL 2001, Winston ETAL 2007, also proves to be critical for further understanding of the subjective neural processes involved in decision-making as well, it turns out, for the understanding of the processes underlying the rating of visual works of art and the pressures and biases involved in doing so. 8.2 Ventromedial prefrontal cortex involvement in evaluation. In this section we describe a group of experiments arising out of recent interest in understanding the subjective processes involved in decision-making, Montague and Burns 2002. These experiments are unified by the theme of hedonic or affective components in the aesthetic rating of a visual work of art. Kawabata and Ziki's research showing that the recruitment of medial OFC in the rating of works as beautiful as opposed to ugly, Kawabata and Ziki 2004, suggested the possibility of examining the question of how preference ratings of works of art are modulated by semantic information presented alongside them. Then Kirk and colleagues designed an fMRI study to measure the influence of cognitive information on the modulation of subjective preference for visual works of art, Kirk ETAL 2009A. In this study, chromatic reproductions of paintings from the Louisiana Museum of Modern Art in Copenhagen were shown to 14 subjects with no formal training in any area of art. They were accompanied by labels below each of them, with half identified as from the Louisiana Museum, gallery label, and half as computer generated by the experimenter, computer label. Pre-screening ensured that no subject had any familiarity with the paintings shown. Using this experimental design, the aim was to determine whether the contextual information, contextual bias and insulation against bias during aesthetic rating 161 supplied would affect the aesthetic evaluation and the subjective preference associated with it, either in terms of the behavioral ratings or of the neural processing underlying them. It was assumed that the gallery label would induce a higher expectation of reward than the computer label, and that this would be reflected both in the behavioral ratings and in the neural activity engaged in the processing of reward. The question was the degree to which subjective preference might be altered and modulated by framing its status as artistic or as merely computer generated. Whatever the direct sensory appeal of a work, the possibility remained that top-down influences would influence coherent behavioral preferences and recruit a specific neural network that differed from those involved in such appeal. The hypothesis was that one's concept of the status of the art object, rather than its sensory properties, would be the underlying determinant of one's subjective preference for one rather the other. This, of course, would be consistent with the now long-standing claim in philosophical aesthetics that there are no inherent properties of an object that constitute it as art, and that its very constitution as art is predicated either on its institutional context or its philosophical status, which in many cases, particularly these days, merge. Dento 1964. Often these are the only criteria, beyond general acclaim, by which works are defined as art or non-art. One might further maintain, consistently with the positions of many contemporary conceptual artists, that it is the labeling of works of art as art that enables them to be experienced as such, precisely as this experiment may seem to suggest. The neural data the experiment provides thus reinforce a central aspect of the new debate around the issue of how art is constituted. What emerges clearly from this study is the influence of explicit contextual information on neural activity in the VMPFC. Given the role of the VMPFC in value computations and in experienced pleasure during experiential tasks, e.g. Anderson ETAL 2003, O'Doherty ETAL 2003, Rolls ETAL 2003, it is perhaps not so surprising that it should be modulated by contextual information. Plassman ETAL 2008, McClure ETAL 2004, Del Rajo ETAL 2005. Research in the field of neuromarketing and marketing actions further clarifies VMPFC activation during decision-making. Moreover, the fact that activity in this area is modulated by contextual information also emerges, for example, in experiments in which subjects evaluate their preference for liquids or odors. One study, Del Raggio et al. 2005, showed that subjects rated a test odor as significantly more pleasant when paired with a pleasant verbal descriptor than with an unpleasant one, and that this correlated with activity in the VMPFC. High-level cognitive input such as word labels clearly influence brain activity in the VMPFC, which plays a critical role in experienced pleasantness. Another study, McClure et al. 2004, investigated the neural systems involved in generating preferences produced by two different brands of soft drinks. They found that the rated preferences for unlabeled drinks, i.e. without cognitive influences but based only on sensory information, correlated consistently with VMPFC activation, while brand knowledge produced a strong influence both on expressed ratings and on measured responses in hippocampus, as one might expect, midbrain, and DLPFC. We shall examine the implications of such DLPFC activation later in this chapter. On the other hand, Plasman and 162 Ulrich Kirk and David Friedberg colleagues recently showed, predictably, that wine ratings are higher when the monetary value of a wine is known than when it is unknown, and that there is a neural correlate of this effect in medial OFC/VMPFC. Plasman et al. 2008. In their examination of the neural correlates of contextual modulation of subjective preference for paintings, Kirk and colleagues found that aesthetic ratings were significantly higher for pictures labeled gallery than those labeled computer. Kirk et al. 2009a. This correlated with greater activation of VMPFC under the gallery than under the computer condition. Given the now well-established role of this area in the representation of experienced pleasure, e.g. Anderson et al. 2003, O'Doherty et al. 2003, Rolls et al. 2003, this is hardly surprising. The correlation of VMPFC activation with the higher aesthetic rating assigned to works under the gallery rather than the computer label coincides with current evidence that VMPFC activation represents the subjective preference response involved in the assignment of aesthetic preference to one stimulus over another. The results derived from this experiment also provide evidence that this representation holds even when the attributed preference ratings are modulated by cognitive and semantic input. Taken together, these findings showing modulation of VMPFC by contextual information suggests an interaction between sensory processes and top-down information in this region. On the other hand, consideration of the neural effects of paintings in the gallery versus computer conditions regardless of aesthetic rating showed increased activation of bilateral parahippocampal gyrus, visual cortex, and bilateral temporal pole. The distinction between these two very different categories of areas of activation calls for comment. Some of the reasons for this difference are clear, others possibly less so. They turn out to be critical to the understanding not just of the cognitive modulation of aesthetic evaluation but also of the role of expertise in suppressing context-induced bias during aesthetic rating. The study by Del Raggio and colleagues of cognitive influences on odor preference showed greater activation in VMPFC when subjects made preference ratings of a set of odors manipulated with a positive word label rather than a negative one. Psychophysical studies had long established the relative inefficiency of olfactory discrimination in humans, to the extent that successful odor identification was known to be highly susceptible to factors such as familiarity and to the semantic connection between an odor and its name. Kane 1979. It is thus hardly surprising that Del Raggio and colleagues should have found that verbal or semantic information had a strong influence on both perception and rating of odor attributes. That semantic labels can influence aesthetic and hedonic ratings of works of art is less well documented, however. Russell found that the introduction of title and artist's name upon second ratings of individual abstract and semi-abstract artworks produced an increase in hedonic value. Russell 2003. Kirk and colleagues' research extended this observation by showing that semantic labels, prestigious gallery versus computer generated, influenced subjective preference, even when there was no difference in the stimulus material. Kirk et al. 2009a. Here too they found a neural correlate in VMPFC for the behavioral evidence, just as Del Raggio and colleagues had found. Del Raggio et al. 2005. Other studies have shown modulation of VMPFC in response to objects of varying reward value. Kirk and colleagues found that cultural objects such as sports cars versus small contextual bias and insulation against bias during aesthetic rating 163 cars modulate reward circuits in male subjects not only the dopaminergic reward circuitry in ventral striatum, but also in anterior cingulate and in median orbitofrontal cortex, in the usual regions overlapping with VMPFC, Kirk et al. 2002. VMPFC is strongly implicated in signaling basic appetitive aspects of reward. Blood oxygen level dependent, both, signal changes in this region correlate with reward value, O'Doherty et al. 2003. VMPFC has also been implicated in emotional processing with increased responses to rewarding outcomes, Lane 1997. The likelihood that it is engaged under conditions that require behavioral decision-making is consistent with its involvement in the integration of reward feedback for effective decision-making, Kringelbach et al. 2003, O'Doherty et al. 2003. This is all very well, but how are these VMPFC results to be interpreted in relation to the question of the neural mechanisms involved in the aesthetic evaluation of visual images, and of art in particular? McClure and colleagues' study showed that brand knowledge of soft drinks influenced activations in hippocampus, primary visual cortex, and dorsolateral prefrontal cortex, areas that have traditionally been regarded as having strong cognitive rather than flavor-related functionality, McClure et al. 2004. In 2009, Kirk and colleagues demonstrated bilateral activation of the entorhinal cortex in the gallery versus computer condition, irrespective of the actual aesthetic rating, Kirk et al. 2009a. This much stands to reason. The entorhinal cortex adjoins and is interconnected with the hippocampus and is activated in trials in which subjects correctly recollect contextual information compared to trials in which they do not, Cancino et al. 2002. Other findings suggest that midbrain dopaminergic systems involved in reward expectation directly modulate declarative memory formation in the hippocampus. This evidence is consistent with our initial hypothesis that it is the subject's conception of the image, rather than its sensory properties, that primarily also determine its hedonic value. This effect might arise from subjects' differing prior expectations of future reward and thus of hedonic value as evoked by the stimulus labels. One could thus account for two possible factors in the gallery versus computer-generated experiment. The first would loosely have to do with relative difference in prestige. Despite recent developments in all forms of computer-generated and cyber art, by and large art galleries remain a more prestigious context both for the display of and as a source of artworks than the internet. In this case, expectation or prediction of reward arises from a social prior. The more prestigious the gallery, the more competition to display works in it, and a sense of the artist's success may well be correlated with a higher degree of reward expectation. A second, closely related factor might be the greater monetary value attached to showing in a more prestigious than a less prestigious gallery, let alone the monetary value attached to a work that is merely said to be computer-generated, but is in fact a reproduction of a real painting, and not displayed in a more or less prestigious gallery. In many cases, especially outside the rarefied contexts of analysis by students of the history of art and critics, a simple social prior is that the more expensive the artwork, the greater the likelihood that it will have a higher hedonic value. Cognitive inputs such as semantic word labels clearly have a profound influence on aesthetic rating. The data summarized above suggest that the entorhinal cortex and temporal pole are engaged during recollection of art-related and cultural information that may influence aesthetic preference during gallery conditions, while the MPFC is more involved in the generation of preference computations. These two systems do not appear to function independently of each other, but are interdependently modulated in such a way as to generate aesthetic preferences as induced by semantic context. 8.3 Neural correlates of aesthetic expertise. A related question is that of the degree to which aesthetic expertise modulates aesthetic evaluation. Many recent studies have demonstrated substantial and deep differences between experts and non-experts in their assessment of works of art, as well as in the neural substrates that underlie their preferences and evaluations. Talbot Marino et al. 2005, Hecker et al. 1996a, 1996b. In 1966, McQuinney showed that subjects without art training generally prefer simple and symmetric visual elements, whereas those with training or background in art tend to favor complex and asymmetric visual elements. McQuinney 1966. In 1990, Smith and Millar concluded, with equal predictability, that music novices show a greater preference for syntactically prototypical chord progressions than do experts. Smith and Millar 1990. Forms of training, not always adequately specified, and degree of expertise are generally said to contribute to these differential preferences. One could always say it is often claimed that training in a particular art, and deeper knowledge, familiarity, and experience, enriches perceived meaning, and it is usually held that experts inclined to respond to aesthetic values, broadly taken, over purely sensory ones. One of the difficulties in the literature so far is that expertise is never clearly defined, nor is it clearly established in exactly what expertise is supposed to consist. Often the rather general supposition is made that experts are more likely than novices to take into consideration concepts of aesthetic value, or the concepts and ideas on which the work is based, or on the supposed, or prevailing, norms of good and bad taste. Smith and Millara 1990, 4-1979. Preferences expressed by experts are often thought to reflect a disposition for distancing oneself from popular taste, as exemplified by non-expert viewers. Often it is believed that aesthetic experience involves the processing, recognition, and broad understanding of an individual style. Some form of stylistic awareness, analysis, and recognition then becomes a critical marker of aesthetic expertise. As is well known, even highly abstract paintings can be constrained by rules, although the underlying principles are not immediately evident to those outside the artist's circle. Kupchak and Laszlo 1992. There is no question that critics and art historians are frequently more aware of the preferred techniques and rules that distinguish one style from another, however, and that this affects their evaluation of the work under consideration. An abundance of evidence points to direct expertise effects in the brain, especially in structures related to memory and perception even on the macroanatomical scale. In a striking voxel-based morphometric analysis, McGuire and colleagues found that contextual bias and insulation against bias during aesthetic grading 165 gray matter volume in the posterior hippocampus of London taxi drivers was greater than in age-matched controls, and seemed to increase correlatively with time spent taxi driving. McGuire et al. 2000. Increasing numbers of studies have been devoted to the role of expertise effects in responses to music. In their fMRI study of 2006, Bangert and colleagues compared brain activity in groups of musicians and non-musicians as they listened passively to a piano sequence, and found elevated levels of activity in the musicians' brains in regions of the temporal lobe associated with auditory processing, as well as in frontal regions associated with motor control. Bangert et al. 2006. More recently, Jacobson and others have taken a different approach to comparing aesthetic responses in experts and laypersons and analyzing ERP effects in the course of auditory and cognitive processing of chord sequences. Raptico and Jacobson 2009. Cf. also Bigand and Poulincharna 2006. As already mentioned, a number of fMRI studies have identified cortical areas recruited during the aesthetic evaluation of pictures. Kawabata and Ziki 2004. Jacobson et al. 2006. Kirk et al. 2008. The results suggest that the computation of preferences largely relies on areas implicated in the processing of reward, especially VMPFC and ACC. To what degree are these reward-related areas modulated by expertise? VMPFC has been found to correlate with subjective preference ratings, and to be involved in coding stimulus value from a variety of sensory modalities. Knudsen et al. 2003, O'Doherty et al. 2003, Rolls et al. 2003, McClure et al. 2004, Glassman et al. 2008. It serves as a critical center both for the tracking of reward value of different stimuli independent of their sensory modality, i.e. taste, smell, etc., and for relating this value to hedonic experience. Although it could be argued that the rules of art, say of 20th and 21st century abstract art, are not effectively equivalent to the technical rules of art or architecture, a further neuroimaging study sought to investigate the extent to which the neural correlates of aesthetic evaluation vary as a function of expertise in architecture. Kirk et al. 2009b. This fMRI study cast considerable light on 1. The question of the impact of expertise on aesthetic preferences, and 2. How differences in assessment strategies between experts and non-experts can be tracked as differences in neural activity. The subjects here consisted of one group professing to have no great interest or expertise in art or architecture, and another group of experts, consisting of graduate students in architecture and professional architects. Each group was asked to rate the aesthetic value of a series of images of architecture, divided between modernist and pre-modernist, public and private, and faces. Aesthetic value was rated on a scale of 1, very unappealing, to 5, very appealing. Kirk et al. 2009b. It was hypothesized that the expert-specific condition, architectural images, would significantly affect both aesthetic ratings and neural activity differentially. Since earlier psychometric studies had found that people in different cultures and of both sexes tend to agree as to which faces were attractive, Langlois et al. 2000, it was predicted that there would be little if any significant differentiation between the two groups' aesthetic ratings of faces and the neural processing underlying such ratings. In other words, it seemed likely that an expertise effect on the neural structures underlying the formation of an aesthetic judgment would be evident when architects rated the buildings, but not when judging faces. 166 Ulrich Kirk and David Friedberg. The behavioral responses, i.e. the aesthetic ratings, for both categories of images revealed no significant differences between the two groups. To test whether architectural expertise modulated brain activity underlying aesthetic preference, an analysis was made of those regions where the difference between the responses for the two stimulus conditions varied across the two subject groups. Significant activations were found in VMPFC and bilateral ACC, but were greater in the case of expert preference ratings of buildings, while remaining essentially balanced across the two groups in the case of face stimuli. The observed effect clearly related to acquired expertise in architecture. Nucleus accumbens, NACC, showed the same level of response in both groups and to both sets of stimuli, regardless of expertise level. This finding thus replicated previous findings that PPMFC and striatal regions, including the NACC, play different functional roles in reward processing. Knudsen et al. 2001, O'Doherty et al. 2003. A plausible conclusion would be that VMPFC processes evaluation of stimuli, whereas the nucleus accumbens is more involved in prediction of reward and reward expectancy, as has often been shown. Montague et al. 2004. Nevertheless, the fact that the VMPFC is sensitive to the magnitude of aesthetic value accords with recent studies showing that the relative reward value of stimuli is reflected by the amplitude of neural activity in this region, whereby we mean that activity in the VMPFC increases linearly with aesthetic ratings. These studies have also indicated that this region codes the reward-related rather than the sensory aspects of a stimulus. Kringelbach et al. 2003. One may go a step further. The data from the study of architectural experts versus novices in rating buildings and faces shows that architectural expertise modulates the neural response to buildings even in the absence of any differences in aesthetic rating between experts and non-experts. This further confirms what may seem obvious, namely, that the expertise effect is specific to the domain of expertise. In conclusion, the results of Kirk and colleagues' study of architectural expertise showed that VMPFC and ACC are differentially engaged as a function of expertise, but that NACC is equally activated in both experts and non-experts. 8.4 The influence of favors on valuation and decision-making. For some time it has been known that decision-making can be biased by the offering of favors, or by particular social gestures. Lowenstein et al. 1993. The tendency to be influenced by biases may be rooted in biological mechanisms that subvert cognitive control. In real-life scenarios, such biases occur where social gestures from a sender to a receiver encourage some equivalent behavior in return, even if the agreement is not explicit. This feature of response is known as reciprocity. It is clear that in many cases open-ended gestures may be made without any explicit expectation of reciprocity. For recent discussions of the neural mechanisms of reciprocity eliciting gestures, see Lilling et al. 2002, King Casas et al. 2005, Lee et al. 2009, and it is in this domain that the whole question of how social gestures may manipulate value judgments arises. So too does the still broader question of how open-loop favors, in which there is no possibility of reciprocating interactions, contextual bias and insulation against bias during aesthetic rating 167 between sender and receiver, affect decision-making and therefore preference judgments. Such cases would seem to be particularly relevant to the case of abstract rewards such as might arise from preference judgments for one painting over another. The use of monetary favors to influence preference offers particularly striking real-world examples of the manipulation of value judgment by perceived external social value. The media often alleges manipulation of drug choice by monetary favors. Cf. also Wasson 2000, Dana and Lowenstein 2003. Harvey and colleagues hypothesized that a monetary favor would affect subjects' preference ratings of works of art. Harvey et al. 2010. It may seem that this sort of favor is a specific and exceptional instance of the external motivation of valuation judgments and rating, but in fact it offers an interesting and critical test case where there is no objectively correct answer, and where the favor is entirely of the open-loop kind, with no possibility of a reciprocal interaction between sender and receiver. Harvey and colleagues' experiment also makes clear not just that monetary favor biases judgment in domains unrelated to the favor, but also that the neural substrate of the brain modulations induced by monetary favor is not separate from the networks activated by preference judgments more generally. Furthermore, while monetary favors may not be thought to be particularly relevant to the case of art, in the present art world it very clearly is, and may always have been. The offer of monetary favor stands as exemplary for a wide range of potential biasing factors in judgments about and ratings of works of art. The case seems particularly applicable to the operations of the art market, but in fact could be seen to apply to any other form of social gesture that elicits reciprocity, for example, the use of pictures as forms of marriage solicitations or proposals, a phenomenon that has a long history, or any other such reciprocal arrangement involving supposed beauty or social benefit. Recent experiments have begun to shed light on the neural mechanisms of reciprocity eliciting gestures. King Causes ETAL 2005, Brillen ETAL 2002, Lee ETAL 2009, Van den Bos ETAL 2009, but almost nothing is known about the influence of an open-loop favor where there is no possibility of reciprocal interactions between the sender and the receiver, or in which one agent makes a gesture or offers a gift without any explicit expectation of reciprocity. Harvey and colleagues hypothesized that the offer of social favors would bias subjective preferences, even for objects unrelated to the favor itself, as in the case of works of art. They addressed this hypothesis by employing a series of monetary favor and preference experiments, in which a total of 151 subjects participated. Before scanning, subjects were told that they would be sponsored for their participation by one of two companies. At the beginning of the fMRI task, they were shown two company logos followed by a screen showing which of the companies would be sponsoring them, as well as the amount of compensation, $30, $100, or $300. During scanning, subjects passively viewed 60 reproductions of paintings, each paired with either a sponsor logo or a non-sponsor logo. After scanning, they provided preference ratings for all the pictures they viewed. In other words, in this experiment, a monetary favor was sent from an agent to a subject, and the influence of this favor on subjects' preferences for one image over another was tested. This is a domain in which there are no objectively correct answers for such preferences, and there is no economic relationship between the favor and the preference judgments. What was striking about this set of experiments is that the mere offer of a favor was able to influence subjective decision-making, even without actually paying the favor out. Responses both in BMPFC and posterior cingulate correlated linearly with the behavioral change across the three offer conditions. Harvey et al. 2010. The behavioral results showed that preference for paintings paired with the sponsoring company's logo was higher than those paired with the non-sponsor logo. The functional imaging results revealed that activity in the BMPFC tracked the value signals of the paintings belonging to the sponsorship category to a higher degree than those that did not thus belong. This really was the first imaging study to indicate that a monetary favor could transfer value to a proxy, and could influence preference judgment of objects that were placed next to the sponsorship logo, with corresponding changes in neural activity. Moreover, the experiment was designed with no reciprocal interaction between the company and the receiver, suggesting that the favor could influence behavior even when the receiver had no explicit expectation of reward in the outcome of the interaction. What is critical about these results is that they show that the sponsorship effects described do not possess a special and separate network of brain responses, but instead modulate responses in neural networks normally activated by a wide range of preference judgments. BMPFC encodes for revealed preference across a whole variety of sensory modalities. Knudsen et al. 2003, Authority et al. 2003, Rolls et al. 2003, McClure et al. 2004, Plasman et al. 2008, Kirk et al. 2009a. Activity within BMPFC suggested that the neural networks normally activated by a wide range of preference judgments are also modulated by the strong effect of sponsorship. The effect is so robust that it is not sensitive to changes such as logo size or distance from the stimuli themselves. The results raise the important possibility that monetary favors bias judgments by acting through existing valuation mechanisms, and that individuals may therefore have difficulty detecting the gesture's influence over their subjective preferences even for objects seemingly unrelated to the favor. 8.5 Mitigation of the effects of favors by domain expertise and follow-up experiments to those of Harvey and colleagues. The same team examined whether the biasing effects of social gestures on valuation judgments could be mitigated. Kirk et al. 2011. In the case of medical professionals, for example, biases from monetary gifts or other favors from pharmaceutical companies are thought to be mitigated by a variety of mechanisms, including disclosure of potential conflicts of interest, not accepting large gifts or favors, and oversight from institutions regarding biases in prescribing behavior. In addition, the fact that medical professionals have expertise in their domain of decision-making is taken as an argument that they should be more objective in their judgments than laypersons making similar decisions. The obvious question for the field of art is the degree to which expertise and experience in art insulates against judgment bias. To test this directly, a group of participants with expertise in the domain of art were recruited to perform the favor task outlined in the previous section. Expertise criteria included a formal education in a visual art-related area and a minimum of 5 years of experience working in visual art-related areas. The hypothesis was that training in assessing art would insulate such subjects against the biasing gesture of the sponsoring company, and that if this were indeed the case, there would be neurobiological correlates corresponding to the differences in behavior between art experts and non-experts. The group of experts was asked to undergo an fMRI scan while viewing images of the artwork, paired either with a sponsor company logo or another non-sponsor company logo. After the fMRI session, each subject rated his or her preference for the art displayed in the scanner. The setup was identical to the previously discussed experiments, except that student art was used rather than well-known paintings, to eliminate the possibility that differences in results between art experts and non-experts were solely a result of familiarity with the paintings. In the behavioral results, there was no difference between experts' preference for sponsored paintings versus non-sponsored paintings, in contrast to the control subjects who showed a significantly higher preference for sponsored paintings. It was hypothesized that if the experts did not show an effect of sponsorship on preference ratings for paintings, bold activity in the BMPFC would also not be sensitive to sponsorship in the way it was in the control subjects, whose behavior reflected the bias towards sponsor-related paintings. This turned out to be the case. While both the control group and the art experts showed activity in the BMPFC correlating linearly with painting preference for all paintings, the experts did not show differential activity in this region for sponsored compared to non-sponsored paintings. However, if the group of art experts showed no effect of sponsorship either on their behavior or on activity in the BMPFC, what region of the brain was involved in the mitigation of this effect? To explore this further, activity in the dorsolateral prefrontal cortex, DLPFC, was analyzed. DLPFC is known to be involved in executive control, Wegner et al. 2001, and in modulation of valuation, in experiments on goal values and the influence of instruction on reward learning, Hare et al. 2009, Lee et al. 2011. The results showed that relative to the control group, viewing artworks elevated activity in the DLPFC, whereas the control group did not show activity in this region. These results indicate that in the expert group, DLPFC was continuously engaged in the regulation of bias susceptibility. In subsequent analyses, right DLPFC turned out to be functionally connected to the BMPFC, and the coupling of these two regions was stronger during presentation of sponsored paintings than during presentation of non-sponsored paintings. As recent studies of the neurobiology of self-control have also shown, BMPFC may indeed be modulated by areas of the DLPFC, especially in instances of self-censorship. Hare et al. 2009. It is clear that DLPFC plays a critical role in self-censoring modulations of neural valuation mechanisms such as the BMPFC. It also serves as a more general mechanism by which a person may be insulated from bias and from biasing maneuvers, rather than being specific to individuals with domain expertise, whether in art or in any other field. What does emerge, however, is that in experts or in those with training in art, DLPFC more strongly modulates BMPFC activation in such a way as to insulate them from the kinds of biases that are generated by contextual information and by reward prospects, whether financial or sensory, or by any other of the kinds of elements that attract both non-experts and experts to a work in the first place. The importance of such results for the ways in which experts are insulated from biasing effects, such as those of possible financial gain, or even of prestige effects, cannot be overestimated. Chapter 9 Neuroimaging Studies of Making Aesthetic Products. Ocean Vartanian. The fields of empirical aesthetics and creativity have largely advanced in parallel. As a result, although we possess fairly sophisticated models that explain how creative production, Ganonyakabi et al. 2013, and aesthetic appreciation, Nadal 2013, are realized in the brain, little is known about how these two processes intersect psychologically or neurologically. Vartanian 2014. This is a peculiar state of affairs because when artists create a work of art, they are concerned about its eventual appreciation by potential perceivers. Similarly, when perceivers experience artworks, they make inferences about the creative processes that led to their production. Therefore, it would appear that a comprehensive model of the artistic process would necessitate not only models of how creative production and aesthetic appreciation unfold, but also an overarching model that relates the two aspects together. As the content of this volume makes readily apparent, neuroimaging data have contributed more to our understanding of the neural basis of aesthetic appreciation than they have to our understanding of the neural basis of artistic production. The reasons for this are primarily methodological. Specifically, in the early days of human neuroimaging research, few methods existed to enable the collection of ecologically valid data in the scanner in various domains of artistic production. Fortunately, technological advances in recent years have begun to change this landscape. See TAM et al. 2011, and some data are now available on the neural systems that underlie the production of aesthetic products in the scanner. Because the neurobiological basis of aesthetic and artistic appreciation as well as neuropsychological studies of artistic production will have been reviewed in considerable detail by various contributors to the present volume, my focus here will be on neuroimaging studies of creative production in the domains of music, Lemon Braun 2008, writing, Shah et al. 2013, and drawing, Elamil et al. 2012. Although there have certainly been studies of the neural basis of other aesthetic behaviors, most notably dance, Brown et al. 2006, see also Brown and Parsons 2008, the focus of the present chapter will be on studies that zeroed in on the neural basis of the creative aspects of generating aesthetic products. My focus here on the creation of aesthetic products, rather than their appreciation, is motivated by the overarching idea that the creation and appreciation of artworks represent neuroimaging studies of making aesthetic products 175 two sides of the same coin, and are intimately linked, CCP 1999. Therefore, our neural models of how people respond to artworks will be augmented by a better understanding of neural models of creative output, and vice versa. I will close the chapter by reviewing Tinio's 2013 Mirror Model of Art, a very promising theoretical model that provides a testable framework that conjoins the creative and aesthetic aspects of art. It is my hope that the introduction of this model will motivate research geared toward bringing together these two facets of the study of art. 9.1 Creative drawing. One of the most enduring distinctions in the literature on creativity involves its two phases, blind variation, i.e. generation, and selective retention, i.e. evaluation, of ideas. Campbell 1960. According to the classic interpretation of this distinction, the generative phase of the creative process is not goal-oriented but instead is rather blind. In other words, the person does a random search through the contents of consciousness to initiate the process, including the combination of previously unrelated ideas and concepts and ideas to form new associations. Thackeray 1913. Although many scholars have since questioned the assumption that this process is truly random, Isaac 1993, Simont in 2011, most agree that the generative phase of the process is where novel combinations of ideas are most likely to occur. In this sense, the generative phase has held much more allure for creativity researchers than the evaluative phase, with relatively less research devoted to the cognitive processes that underlie evaluation, but see Vartanian et al. 2009. Neuroscientific studies of creative problem solving have also attempted to isolate the neural basis of generation versus evaluation. For example, Goel and Vartanian, 2005, demonstrated that the right ventral lateral prefrontal cortex, PFC, and left dorsal lateral PFC were activated to a relatively greater extent in the generation versus evaluation of matchstick problems, a well-established paradigm for studying divergent thinking, Guilford 1967. Furthermore, additional analyses demonstrated that the activation of right ventral lateral PFC could be attributed to its involvement in set shifting or lateral transformation processes, i.e. breaking of conceptual or perceptual constraints imposed on the task. This interpretation is supported by a large body of neuropsychological and neuroimaging data implicating the right PFC in the generative phase of creative problem-solving tasks, e.g. Miller and Tippett 1996, ill-structured design tasks, e.g. Goel and Grafman 2000, and well-structured problem-solving tasks, e.g. Newman et al. 2003. Thus, although the neural basis of creativity is known to be distributed in the brain, Ganonyakabi et al. 2013, the lateral aspects of right PFC appear to play an important role in the generative phase of creative problem-solving, especially in cases where this involves breaking the constraints imposed on the problem. Elamil and colleagues, 2012, implemented an ingenious experiment in a functional magnetic resonance imaging (fMRI) scanner to dissociate the generative and evaluative phases of creative drawing. This was made possible by their use of an MRI-compatible tablet, TAM et al. 2011, enabling the participants to draw on the digital device. Importantly, 176 Ocean Vartanian participants were undergraduates from the Emily Carr University of Art and Design. In other words, they had training and experience in the visual arts. The experiment consisted of two key blocks, as well as additional baseline blocks. The generate block began with the visual presentation, using words, of book descriptions involving abstract concepts, e.g. war, immigration, religion, and participants were instructed to draw and write their ideas for a corresponding book cover using the MRI-compatible tablet. Then, in the evaluate block, they were instructed to draw and write their evaluations of their book cover ideas, again using the MRI-compatible tablet. Following the termination of a specific number of generate-evaluate cycles, the participants were prompted to talk about their assessments of how well they were able to engage in generation and evaluation of these book covers. Here I will focus on a subset of the findings most relevant for our purposes. The generate-evaluate contrast, what is unique about generation over and above evaluation, revealed greater activation extensively in the medial temporal lobes, MTL, bilaterally, including the hippocampus and the parahippocampus. In addition, activations were observed bilaterally in the inferior and superior parietal lobule, fusiform gyrus, middle temporal gyrus, and the premotor area, as well as left inferior frontal gyrus and cerebellum. In contrast, evaluate generate contrast, what is unique about evaluate over and above generation, revealed greater activation in a large distributed network including regions within the executive network such as dorsal anterior cingulate cortex, ACC, and bilateral dorsal lateral PFC, regions within the default network including medial PFC, posterior cingulate cortex, bordering on precuneus, and right temporoparietal junction, and bilateral rostrolateral PFC, bilateral cerebellum, bilateral. Temporopolar cortex, left anterior insula, supplementary motor area, bilateral inferior frontal gyrus, bilateral superior parietal lobule, bilateral middle temporal gyrus, bilateral lingual gyrus, bilateral middle occipital gyrus, and bilateral cuneus. In addition, based on their subjective reports, for each phase the investigators assessed the degree of correlation between the activated regions and success in the respective task. The analyses revealed that in the generate condition, activation in MTL regions including the hippocampus and parahippocampus was correlated with perceived success, whereas in the evaluate condition, activation in executive function and default network regions was correlated with perceived success. The results revealed that MTL regions, specifically the hippocampus and parahippocampus, contribute to the generation of ideas during creative drawing. The involvement of MTL can be attributed to at least two sources. First, MTL is known to play an important role in the formation and retrieval of semantic and episodic associations, Honk et al. 1999, and its involvement here is consistent with the role of associated processes in creative cognition, Mednick 1962. However, another intriguing possibility is suggested by the composition of the sample. Remember that the participants recruited in this study were not new to drawing. In fact, they were university students majoring in the visual arts. As such, it might also be that the activation observed in MTL during idea generation might be due to the mnemonic recall of relevant information stored in long-term memory, also a well-established function of MTL. Importantly, these two possibilities are neuroimaging studies of making aesthetic products 177 not mutually exclusive, and point to the important role of MTL in the generation phase of creative drawing, at least in trained and experienced participants. Compared to the generative phase of creative drawing, the evaluative phase was associated with activations in executive function and default network regions, among others. The involvement of the executive function region is not surprising, given that cognitive control in the service of analytic processing would appear to play an important role in judging the quality of generated products. Dosenbach et al. 2008. By contrast, at first glance the involvement of the default network region is surprising. However, Elmore and colleagues, 2012, argued that its involvement in the evaluative phase is less surprising when one considers the broader role of this network in the processing of internally generated, effective information. Buckner et al. 2008. When viewed as such, the default network's role could be to perform inductive inferences based on internal effective information to draw conclusions that guide behavior. P1790, in this case opting to select or discard a generated idea, i.e. drawing or writing. In conclusion, the results of Elmore and her team, 2012, demonstrate that the generative and evaluative aspects of creative drawing involve dissociable neural systems. This is consistent with the idea that these two phases involve different sets of mental processes. Importantly, by elucidating the involvement of the default network in the evaluative phase, the results of this study illustrate the value of neuroimaging data in improving our understanding of the creative process underlying the generation of aesthetic products. Specifically, the results point to a possible role for effective processes in evaluating the quality of aesthetic products, a process not emphasized by any of the main generate-evaluate models of the creative process. See Campbell 1960, Eisen 1993, Simont in 2011. 9.2 Creative writing. Few endeavors are as quintessentially creative as writing. In this sense, the fMRI study conducted by Shaw and coworkers, 2013, is a welcome addition to the family of studies on the neural basis of creative production. Unlike the research undertaken by Elmore and colleagues, 2012, who were motivated to dissociate the neural systems underlying generation and evaluation in creative drawing, Shaw's team's experiment was designed to test Flower and Hayes, 1981, model of writing. According to this model, the writing process can be broken down into three stages: planning, translating, and reviewing. The planning stage involves generating ideas based on the contents of long-term memory. The intermediate stage of translating involves transcribing those ideas into text based on linguistic rules. Finally, the reviewing stage consists of the evaluation of the written text, possibly involving revision. Clearly, Flower and Hayes, 1981, three-stage model shares much in common with Camel's, 1960, two-stage model, where the only, explicitly, missing part is translation. I suspect this is because Camel's model was not meant to be domain-specific, and was therefore made to account for all types of creativity, each of which would, obviously, engender their own domain-specific translation rules. Nevertheless, despite their superficial differences, it is clear that the results of Shaw and her colleagues 178 Ocean Vartanian and Elmore and her team's work can be compared to examine whether any aspect of the neural basis of the creative process is shared in spite of differences in the specific domain under consideration. Shaw and colleagues, 2013, recruited 28 participants, none of whom had no special training in creative writing. Elmore's team, 2012, had employed an MRI-compatible tablet to record drawings and writings inside the scanner, whereas Shaw's team, 2013, used a design where the arm of the participant was extended outside the scanner to enable writing on paper, and was positioned to minimize movement artifacts. The design consisted of four phases: A. Covered reading of a text, and B. Copying part of the read text, both of which functioned as control conditions. The theoretically interesting phases were C. Brainstorming, and D. Creative writing. In the brainstorming phase, participants were instructed to think how they might continue the passage without actually writing any of it down. Finally, in the creative writing component, they were instructed to write an original but appropriate continuation of the given text. They were allowed to think beyond ideas generated during brainstorming if they wished. P1090. These instructions were used to mimic the phases of creative writing as closely as possible, a process where modifications to the product, writing, are commonly made. Flower and Hayes 1981. Here I will focus on brain activations during the phases of brainstorming and creative writing. The brainstorming phase was associated with a distributed network, more strongly activated in the left hemisphere, including the left inferior frontal gyrus, BA44, 45, and 47, the left dorsolateral PFC, BA946, and dorsal ACC, and sizable temporal parietal cluster of regions, including Wernicke's area, BA3940s, BA22, superior temporal sulcus, extending to anterior temporal regions, BA38. The left inferior frontal gyrus, BA44, 45, and 47, is known to play a key role in language processing, production, and verbal fluency. Price 2010. Its involvement here is not surprising, given that the research explicitly instructed the participants to engage in verbal, linguistic, creativity. In addition, left dorsolateral PFC, BA946, and dorsal ACC are key regions in the brain's executive function network and are critical cogs for planning and cognitive control. Their activation here suggests that during brainstorming, the participants were engaged in some level of selective retention and pruning of the fruits of the generative process, based on the self-imposed criteria of the quality of writing that they sought. Finally, the temporal parietal cluster of regions, extending to anterior temporal regions, is another well-established region in language processing, including sentence comprehension and word association. Price 2010, and its activation here suggests that functions of these regions were related to the flexibility of thinking and involved in imagination and fantasy. Shaw et al. 2013, P1096. In other words, the involvement of this region in brainstorming can be attributed to its role in the formation of potentially distant, linguistically derived, conceptual associations. In turn, the creative writing phase was associated with activation in motor areas including the primary motor cortex, bilateral secondary motor areas, and corresponding somatosensory areas. In addition, frontal activations were observed in the bilateral inferior frontal gyrus, BA44, 45, 47, and left dorsolateral PFC, BA46, as well as activations in the temporal lobes including the posterior part of the superior temporal gyrus, BA22, neuroimaging studies of making aesthetic products 179 superior temporal sulcus, among others. The involvement of the motor areas can be attributed to the realization of motor movement in the service of the mechanics of writing. As was the case with brainstorming, the involvement of the left dorsolateral PFC, BA46, points to the role of cognitive control processes for selecting the products of the brainstorming phase for actual writing. In addition, the involvement of the left inferior frontal gyrus and the specific regions in the temporal lobes can be attributed to their role in linguistic processing and their contribution to creative writing. Summarizing their results, Shaw and colleagues, 2013, noted that creative writing can be understood as translating the conceptual and verbal ideas into a handwriting process after selection, semantic integration, and motor coordination. P1097. Do these results shed light on Flower and Hayes, 1981, model of writing? Remember that according to that model, the writing process can be broken down into the three stages of planning, translating, and reviewing. By and large, the results support this view. Remember too that according to that model, planning involves generating ideas based on the contents of long-term memory. The main effect of brainstorming would appear to support this notion, given that it activated a core set of structures involved in language and memory. In addition, the involvement of the left dorsolateral PFC, BA946, and dorsal ACC in brainstorming can be attributed to their contribution to planning and cognitive control. In turn, translating was hypothesized to involve transcribing those ideas into text based on linguistic rules, which appears to be reflected by the observed activations in motor areas during creative writing. Reviewing may be reflected in frontal activations observed during both brainstorming and creative writing conditions. Furthermore, Shaw and colleagues, 2013, argued that their study also sheds light on the role of domain specificity in the creative writing process. Specifically, they argued that their results revealed The importance of domain-relevant knowledge for creative writing, including language processing, working memory functions, and predominantly, the memory system, episodic and semantic memory retrieval and the semantic integration in an original and coherent story concept. Furthermore, free association and spontaneous cognition are typical characteristics for actual story writing. P1097, thus, as has been suggested elsewhere, Vartanian 2012, although there are certain cognitive functions and corresponding neural structures that can be expected to be operational in most instances of creativity, e.g. working memory, there are likely to be other regions whose involvement will be determined by the specific content and/or context under consideration, such as linguistic regions that operate on verbal material or draw on linguistic knowledge. 9.3 Jazz improvisation. Neuroscientists have long been interested in the brain basis of musical perception and appreciation, as evidenced by studies conducted on the experience of musical chills in response to hearing particularly evocative pieces of music. Blood and Zeta 2001. 180 Ocean Vartanian. Much less is known about the neurobiology of musical production, specifically its creative components. Toward this end, Lim and Braun, 2008, conducted a study to examine the neural basis of the creative component of musical performance in the context of jazz improvisation. Improvisation is a form of spontaneous musical performance defined as the immediate, online improvisation of novel melodic, harmonic, and rhythmic musical elements within a relevant musical context. Lim and Braun, 2008, P1. A major aim of their study was to attain a high degree of ecological validity, recreating an environment during data collection that mimics critical aspects of jazz improvisation in real-world settings as closely as possible. For this purpose, they recruited 6 skilled professional jazz musicians, all of whom were highly proficient at playing jazz piano. They underwent fMRI scanning while improvising, using an MRI-compatible piano keyboard. Data were collected under 2 conditions, one that was relatively high in musical complexity, and one that was relatively low. In the control condition of the low complexity condition, participants repeatedly played an octave C major scale in quarter notes. In turn, in the corresponding improvisation condition, they improvised a melody, but they were restricted to the use of C major scale quarter notes within the same octave. For the high complexity condition, i.e. jazz paradigm, participants were asked to memorize an original jazz composition prior to the skin date. In the corresponding control condition, they played the composition with the auditory accompaniment of a pre-recorded jazz quartet. In contrast, in the corresponding improvisation condition, they were given freedom to improvise, using the chord structure of the composition and the same auditory accompaniment as the basis for improvisation. Here the focus will be on a subset of the findings. First and foremost, improvisation in both paradigms, i.e. high and low complexity, was associated with widespread deactivation in PFC, specifically in dorsolateral PFC and lateral orbital PFC. In turn, this was combined with activation in medial PFC, specifically in BA10. In addition, activations were also observed in sensory-motor areas, as well as deactivations of limbic activity in the amygdala and the hippocampus. This pattern of brain activity tells a rich tale about the cognitive and affective processes that underlie jazz improvisation. As discussed earlier in this chapter, the lateral aspects of PFC, specifically dorsolateral PFC, are heavily implicated in planned behavior and reflect the involvement of executive function and cognitive control. The fact that they were deactivated during improvisation suggests that this activity is associated with a reduction of the top-down control mechanisms that normally govern planned behavior. In contrast, activations were observed in BA10, an area strongly associated with autobiographical narrative, the self, and internally generated cognitions. Buckner et al. 2008, Christoph and Gabrieli 2000. According to Lim and Braun, 2008, this pattern suggests that creative intuition may operate when an attenuated DLPFC no longer regulates the contents of consciousness, allowing unfiltered, unconscious, or random thoughts and sensations to emerge. Therefore, rather than operating in accordance with conscious strategies and expectations, musical improvisation may be associated with behaviors that conform to rules implemented by the medial PFC outside of conscious awareness. P4. Neuroimaging studies of making aesthetic products. 181. The important message here is that improvisation is facilitated by the dynamic interplay between systems that place opposing constraints on cognition. The emerging picture is also consistent with the idea that jazz improvisation is born out of the realization of a personal voice, in this case neurally mediated by medial PFC. That strong activations were observed in sensory-motor, premotor, and motor areas, as well as selective activation during improvisation in supplementary motor areas and portions of the primary motor cortex is consistent with the idea that the mechanics of jazz improvisation are accompanied by the engagement of the brain's motor circuitry and point to domain specificity in the neural correlates of creative production. Finally, the modulation of activity in the limbic system is also informative, although future studies are needed to determine the contributions of reduced activation in the amygdala and the hippocampus to jazz improvisation. In summary, the results of Lim and Braun, 2008, paint a rich picture of the neural basis of creative musical performance among highly skilled performers, and point to the interactive effect of various neural systems to this activity. 9.4 Artistic creativity. Thus far I have reviewed the results of 3 neuroimaging studies on the brain basis of creative production in the domains of drawing, writing, and musical performance. As mentioned earlier, there is a great degree of domain specificity in the observed patterns of activation. For example, creative generation in the domain of drawing was reflected in activation in the MTL, Elmil et al. 2012, whereas creative writing was associated with widespread activation in regions that underlie language, Shaw et al. 2013, and creative jazz improvisation activated the motor and sensory motor regions particularly strongly, Lim and Braun 2008. These activations can be broadly understood as context effects, i.e. reflecting the specific content or activities associated with the target task under consideration. However, it is important to note that in each case the observed activations might also reflect other processes. For example, in relation to the activity observed in the motor regions during jazz improvisation, Lim and Braun, 2008, noted that rather than reflecting an increase in motor activity per SE, these activations may be associated with encoding and implementation of novel motor programs that characterize spontaneous improvisation. In other words, these domain-specific activities might contribute to the creative aspects of performance over and above their supplementary, supportive contributions. Equally importantly, certain regions appear to contribute to creative production across modalities. Chief among those are the dorsal and lateral aspects of PFC. It is well established that these regions play a key role in planned behavior, including executive function, inhibition, and cognitive control. Their involvement in various types of creativity, whether in the form of activations or deactivations, reflects their domain general contributions to creative production. Vartanian 2011. The available evidence suggests that creative production in various domains is born out of the interaction between domain general systems such as dorsal and lateral PFC and domain-specific systems that are critical for the target type of activity under consideration, e.g. drawing. 182 Ocean Vartanian 9.5 Mirror model of art. This chapter began with a call toward the development of an overarching model that can bridge the two sides of the coin, artistic production and aesthetic appreciation. This bidirectional model can be used to study the communication of intended ideas from the creator to the audience via the medium of the work. Recently, a significant advance in this direction was taken by Tainio, 2013, in the form of his mirror model of art. The explicit aim of this model is to provide a verifiable theoretical framework that conjoins the creation and perception aspects of art. The basic premise of the model is that the temporal sequence of art perception mirrors the temporal sequence of art creation. As a result, the psychological processes the perceiver engages in during the early stages of art perception mimic the psychological processes the creator is engaged in during the late stages of art creation, and vice versa. The evidence supporting this model comes from 2 sources: direct observation of artists at work, and the retrospective studies of archival material from artists. Locker 2010. Both of these approaches have converged to show that the creative process in the visual arts occurs in 3 stages. In the first stage, initialization, the artist explores the viability of various ideas. At this stage, sketching can play a key role because it enables the artist to develop emerging ideas, leading to a basic structural configuration of the painting. This basic structure is reflected in the underdrawing of the painting. During the initialization stage, ideational flexibility is key. In the second stage, expansion and adaptation, the artist fine-tunes and reworks the underdrawing. At this stage, the characteristics of the objects and the subjects in the painting undergo numerous changes, reflected in modifications that are made to specific elements of the work. In the third and last stage, finalizing, work on major structural elements of the artwork stops, and time is devoted to enhancing the surface layer of the work in preparation for viewing. Here, focus is shifted to color and texture elements that are likely to grab the viewer's attention first when encountering the artwork. Critically, the artist communicates ideas to the perceiver via various layers of materials that will be encountered in reverse order by the perceiver. In this sense, the medium, i.e. layering, functions as a communicative tool that mirrors the stages in reverse order. The concept, i.e. the initial idea, that triggered the piece is encapsulated in the work conducted during initialization, and represents the final destination in the viewer's journey toward discovering the essential meaning of the artwork. This is because when a perceiver first encounters an artwork, he or she is likely to engage in early automatic processing of low-level features such as color and contrast that are driven by the surface characteristics of the artwork. Chaturji 2003, letter ETAL 2004, features that were added during the finalizing stage of creation. The next stage of perception involves intermediate memory-based processing of content and style, driven by elements such as objects that were modified during the intermediate expansion and adaptation stage of creation. Finally, during the last stage that corresponds to meaning-making and the generation of aesthetic judgments and emotions, the focus is on deciphering the intentions of the artist for creating the artwork. This neuroimaging studies of making aesthetic products 183 is a higher-order cognitive state that draws from the structural organization, i.e. underdrawing, of the painting. 9.6 Aesthetic processing in the brain. Tinios, 2013, model suggests that aesthetic appreciation is a process that begins with an analysis of the surface characteristics of visual artworks such as color and contrast, eventually moving by memory-based processing of content and style to the deepest level of analysis involving the underlying meaning of the work, both personal and cultural. To date, no neuroimaging study has investigated the temporal dynamics of aesthetic appreciation to test this progression. However, it is true that typically experimenters have only provided subjects with mere seconds to view each individual stimulus, i.e. painting, during data collection. Assuming that the three stages described by Tinio, 2013, unfold largely in sequence, rather than in parallel, one can conclude that most neuroimaging studies of aesthetic appreciation to date have only isolated brain structures that are most likely to contribute to the early and intermediate stages of exposure to artworks, rather than the later stages that are most likely require more time than mere seconds for meaning extraction. Consistent with this possibility, a recent quantitative meta-analysis of 15 fMRI studies conducted by Vartanian and Scott, 2014, has demonstrated that the act of viewing paintings was correlated with activation in a distributed system including the occipital lobes, temporal lobe structures and the ventral stream involved in object, fusiform gyrus, and scene, parahippocampal gyrus, perception, and the anterior insula, key structure and experience of emotion and reward. In addition, activation was also observed in the posterior cingulate cortex bilaterally part of the brain's default network. Primarily, the isolated regions underlie visual representation and object recognition, emotion, and reward processing, and representations of internalized cognitions. The picture that emerges supports the idea that activated regions are more likely to contribute to early and intermediate rather than late processing and painting viewing. As noted by Nadal, 2013, determining how the neural network that underlies the experience of art is impacted by personal and cultural meaning constitutes an important challenge to the field. In turn, this will facilitate the development of a framework for connecting the neural foundations of the experience of art to the neural foundations of art creation. 10.1 Introduction. Imagine the following situation. You arrive at the train station bright and early on a Friday morning to start your usual commute into the office. As you cross the main concourse, the train platform departure announcements fade out and are suddenly replaced by the opening lyrics to the Isley Brothers' 1959 classic song Shout. At the same time, a lone figure in the middle of the concourse bursts into energetic dance. A moment later, a woman behind him casts aside her shopping bags and joins in, just as two middle-aged men in dark suits with briefcases kick up their heels and join as well. Within seconds, it appears the entire concourse has come alive with everyday commuters dancing with incredible energy, precision, and joy as they spin, kick, twist, and jazz hand their way through a mashup of decades worth of popular songs. You and the seemingly dwindling crowd of those whose bodies are unfamiliar with this captivating choreography watch in amazement, as the faces of all the ordinary commuters light up with delight to be surrounded by this spontaneous injection of song and dance into a public place. For those of us who were not present at London's Liverpool Street Station on January 15, 2009, this flash mob, filmed as an advertisement for T-Mobile, can be witnessed on YouTube. See. For those who were there, as well as the rest of us who watch online, witnessing a dancing flash mob is something that most people find thrilling. A flash mob is defined as a spontaneous public performance, usually a dance, that appears seemingly out of nowhere with just one person, grows to hundreds of people, then quickly disappears. The Liverpool Street Station example is one of many, from dance performances of Durimi in the Antwerp train station to Gangnam Style in a Jakarta fountain to Love Shack on Bondi Beach. The flash mob is gaining momentum as a much loved, often reproduced way to bring excitement, levity, and even a little bit of art into people's lives where they might least expect it. As I explore in this chapter, one possible explanation for the flash mob's success and appeal is that it transforms seemingly normal pedestrians to extraordinary performers through dance. Throughout history, dance has maintained a critical presence across human cultures, defying barriers of class, race, and status. Dills and Albright 2001. The co-evolution of dance with the human race has fueled a rich debate on the function of art and aesthetic experience, engaging numerous artists, philosophers, and scientists. While dance shares features with other art forms, one unique attribute is that it is expressed, only, through movement of the human body. Because of this, social scientists and neuroscientists are turning to dance to help answer questions of how the brain coordinates the body to perform complex, precise, and beautiful movements. For example, when we watch a ballet dancer leap through the air in a perfect split or break dancer perform 5 consecutive head spins, how might our own dance abilities, or lack thereof, influence how we perceive performers who excite and impress us? In this chapter, I explore how research with dancers and dance learning paradigms can help illuminate issues related to artistic creation and aesthetic preferences, and also consider more fundamental questions concerning the relationship between action and perception. I begin with a section that briefly summarizes the development of a multidisciplinary field whose aim is to explore how action production informs action perception, with a special emphasis on how studies with dancers have advanced this line of inquiry. Next, I focus on a specific conceptualization of the inverse of this relationship, namely, how simple observation of actions can profoundly influence an observer's motor repertoire. Here again, pioneering work using dance underscores how powerful visual experience can be in shaping our motor abilities. While the first two sections mainly use dance as a means for exploring fundamental links between action and perception, the final two sections explore the utility of dance as an art form to inform our understanding of an observer's aesthetic experience of watching another body in motion. After a cursory introduction of issues of concern when studying the aesthetics of action in the penultimate section, the final section explores the relationship between observers' experience and the dancers they behold, in an attempt to establish connections between the two, and in so doing, perhaps help us to understand why we might derive so much pleasure from being caught up in a flash mob in person or watching one on the internet. 10.2 The shaping of perception by action. While we are inclined to take it for granted, our ability to use perceptual information about other people's movements to inform our subsequent actions is essential for successful interactions with the environment, and thus, for survival. Consequently, it is no surprise that inquiry into how the human brain negotiates the path between action, execution, and perception has intrigued venerable thinkers throughout the millennia, including beautiful embodiment 191 Aristotle, Descartes, and William James. Until the mid-19th century, thinking about this relationship was dominated by the Cartesian sensor-motor view, which advanced the idea of independence between action perception and action production. Descartes writing in 1664, as discussed by Prince 1997. As knowledge about the human brain continued to accrue, pioneering scholars began to explore the idea that perceptual processes might indeed converge or overlap to some extent with motor performance. James 1890. Empirical investigation into the brain's ability to use perceptual information to shape movement began in the mid-20th century, when information processing explanations proposing complex transformations from perception to the organization and execution of action gathered momentum. Massaro and Friedman 1990, Mountcastle et al. 1975, Mountcastle 1975, Sanders 1967, 1983, Welford 1968. In the mid-1970s, Mountcastle and colleagues began the first investigations into putative neurophysiological mechanisms linking action and perception. Mountcastle et al. 1975, Mountcastle 1975, Yin and Mountcastle 1977. In these seminal studies, Mountcastle and colleagues used single-unit recording techniques to track the activity of neurons within the superior parietal lobule and posterior parietal areas of the macaque cerebral cortex while the animals performed simple behavioral acts in response to sensory stimuli. In one such study, Mountcastle and colleagues investigated the specific properties of neurons in the posterior parietal association cortex and determined that these neurons respond to visual stimulation to encode the meaning of an action, such as the goal of the perceived movement. Mountcastle et al. 1975. These researchers concluded that this region of the parietal cortex is a likely candidate for cross-modal convergence of perception and action, and established the foundation for the next several decades of further inquiry into how these modalities interact. Anderson et al. 2004. In the 1990s, research into the intersection of action perception and production experienced an extraordinary surge in interest that was due in large part to the discovery of so-called mirror neurons in the ventral premotor cortex of the monkey. These neurons were found to discharge in a similar manner both when a monkey performed an action as well as when it observed another monkey or human perform the same action. De Pellegrino et al. 1992, Galeazzi et al. 1996, Rizzolatti et al. 1996. As such, these specialized neurons have prompted these researchers and others to propose that action perception and production processes form a bidirectional, interactive loop within the primate brain, and that action understanding might be explained by the observer's brain simulating the observed movements of another individual. Fediga et al. 1995, Fediga et al. 1999, Grafton et al. 1996, Rizzolatti et al. 2001. This hypothesis has sparked hundreds of studies and an ongoing lively debate among researchers regarding the specific parameters, scope, and limitations of such an action simulation system within the human brain. Galeazzi et al. 2011, Galeazzi and Sinigaglia 2011. While an exhaustive review of the past decade and a half of research undertaken in this domain is beyond the scope of this chapter, the interested reader is directed to several outstanding overviews of this work, such as those by Grobroz et al. 2012, Mullenbergs et al. 2012, Rizzolatti and Sinigaglia 2010. What a burgeoning corpus of research demonstrates 192 Emily S. crosses that neural tissue found within parietal and premotor cortices of the human brain is engaged when actions are performed or when they are observed. This work has given rise to the notion of a human mirror system, which comprises multiple cortical regions and shows evidence for behaving in a similar manner to individual mirror neurons identified within non-human primate brains. Mullenbergs et al. 2012. In our laboratory, however, our research focuses on what we term the Action Observation Network, AON, Cross et al. 2009, Grafton 2009. The AON comprises those brain regions implicated in the human mirror system, and shown to contain mirror neurons in monkeys, as well as broader swathes of premotor and occipitotemporal cortices, figure 10.1. The interest I have in this network and its role in motor learning and performance is perhaps best summed up by Scott T. Grafton, who said what is striking about this network is that a perceptual stimulus can lead to such a large-scale recruitment of the brain with a complete disregard of textbook divisions between sensory and motor portions of the cortex. Grafton 2009, P100. The bulk of research conducted on the neural correspondence between action and perception, across human and non-human primates, has focused on small, constrained movements of the hands and fingers. Cf. Grobroz et al. 2012, Rizzolatti and Sinigaglia 2010. However, my colleagues and I have devoted a considerable amount of attention to investigating the neural underpinnings of dance performance and perception, which at first might appear to be rather far removed from simple hand and finger actions. However, we use dance to study the AON for three main reasons. First, for most of us, daily life requires the efficient coordination of the entire body, not just the fingers and hands. Thus, dance provides a variety of ideal paradigms for studying whole body coordination. Secondly, dance is generally not object-directed, and thus enables the study of movement for movement's sake, where the goal of an action is the action itself, rather than opening a bottle, tying a shoelace, etc. Finally, by studying a motor behavior that is much more complex and requires the coordination of multiple effectors, we are better placed for understanding a broader range of motor behaviors, from the simple to complex. Such an approach should, in turn, foster greater understanding of failures of the sensory and motor systems, such as those caused by neurological injury. Thus, we turn to dance as a useful means of exploring the impact of action experience on perception. The first study to use dance to explore the relationship between action and perception was the seminal work by Beatriz Calvamarino and colleagues. These authors investigated how highly specialized physical training in one dance style, classical ballet or capoeira, influenced perception of the familiar dance style compared to the unfamiliar dance style. Calvamarino et al. 2005. See also Chapter 11, this volume. The authors reported that when trained ballet dancers watched ballet, or when trained capoeira dancers watched capoeira, greater activity was seen throughout the AON, compared to when ballet dancers watched capoeira or capoeira dancers watched ballet. The authors interpreted this as evidence that years of physical practice shape action resonance processes that occur within sensory-motor cortices active during action perception and action production, such that they are finer tuned to respond to movement that is familiar due to extensive physical practice. Beautiful Embodiment 193 is the study by Calvamarino and colleagues, 2005, was underway. My colleagues and I were addressing a similar question, with additional interest in whether it is possible to track the emergence of motor expertise in something closer to real-time with expert dancers. Cross et al. 2006. In our study, we followed an ensemble of expert contemporary dancers as they learned Laura Dean's 25-minute piece entitled Skylight, Dean 1982, across an 8-week rehearsal period. We invited the dancers into the laboratory for 6 consecutive weeks to scan their brains with functional magnetic resonance imaging, fMRI, as they watched and imagined themselves performing short segments of choreography from Skylight, as well as kinematically similar dance movements that were never seen or rehearsed in the studio. Across the rehearsal period, dancers unsurprisingly became more adept at physically performing the choreography they rehearsed in the studio each day. However, the most interesting finding to emerge from this longitudinal study is that as dancers became more adept performers, activity within two core regions of the AON, left inferior parietal lobule and left ventral premotor cortex, showed increased activity during observation. The better dancer was at performing a particular sequence. We took this as evidence that the better one is at performing an action, the more one embodies it, as demonstrated by increased parietal/premotor activity tracking with increased performance ability. Cross et al. 2006, although see also Cross et al. 2012, for an updated account of the relationship between the magnitude of AON response and motor familiarity. Since these two early studies investigating the brains of expert dancers, a number of research teams have combined dancers with brain imaging techniques. Brown et al. 2006, Forbes et al. 2008, and behavioral paradigms. Calvamarino et al. 2009, Joel et al. 2011, Stevens et al. 2010, and innovative ways to eliminate further how highly skilled movement repertoires influence perception of others. For a comprehensive overview, the interested reader is referred to Blazing et al. 2012. However, from the earliest conceptualizations of action-perception coupling, it has been asserted that not only does action influence perception, as we have seen with the expert dance studies in this section, but perception also influences action. Prince 1990. The following section examines how dance paradigms help illustrate the impact of perception on action. 10.3 The shaping of action by perception. While it is an indisputable fact that one's prior motor experience influences how one sees the world, Prince 2006, how we see others moving around us also shapes our own interactions with the environment. In particular, we rely heavily upon our visual system to help us learn new actions. One of the hallmark ways in which we learn new skills in life, from baking a cake to dancing the tango, is by watching others. Flynn and White in 2010. Behavioral research on action learning suggests that simultaneously observing and reproducing a pattern of movements results in the quickest and most accurate learning. E.g. Baydetz et al. 2006, Bandura 1977, 1986, Blendon et al. 1999, Blendon and Proto 2000, Schmidt 1975, Sheffield 1961. Nevertheless, the ability to learn a new skill or improve an existing one by observation alone, without concurrent practice, is also a powerful capacity in humans. Matter and Gribble 2005, Torriero et al. 2007. 194 Emily S. Cross Early Behavioral Investigations of Observational Learning by Sheffield, 1961, led to the proposal that observation of a motor sequence improved learning by providing a perceptual blueprint, or standard of reference for how the task should be performed. Behavioral studies comparing observational and physical learning support the value of a perceptual blueprint. Blendon and Proto 2000, Carroll and Bandura 1990, Doty et al. 1985, Lee et al. 1990, Seals and Spring 1976. While the bulk of observational learning research has focused on learning from an expert human model, see Hodges et al. 2007 for a review. The use of a human actor performing the target behavior is not a requirement for forming a perceptual blueprint. A more inclusive conceptualization of observational learning encompasses encoding any instruction, whether physical or symbolic, that can provide a sufficient model of the actions to be performed, e.g. Chisek and Kolaska 2004. The key distinction of what defines observational learning is the subject not performing concurrent physical practice at the time instructions are provided. In a study using psychophysical and electromyographic (EMG) measures with human participants, Matter and Gribble, 2005, demonstrated that participants' learning of a novel, complex motor task was facilitated if they previously observed another individual learning to perform that same task, compared to watching another individual perform the task without learning or learning to perform a different task. This established the specificity of a perceptual blueprint formed during the observational period on subsequent physical practice. What emerges from these studies and others: Barzoka et al. 2007, Bouquet et al. 2007, Ferrari 1996, McCullough et al. 1989, Schmidt and Lee 2005, is the hypothesis that observation of movement sequences in physical rehearsal share common cognitive mechanisms, and training of this circuit by either means improves novel motor skill learning. Evidence from non-human primate neurophysiology as well as psychophysical and EMG work with humans suggests that physical and observational learning might share common neural substrates, at least in terms of mental rehearsal. Chisek and Kolaska 2004, Frey and Gary 2006, Matter and Gribble 2005, Wiggett et al. 2012. In one such study, Chisek and Kolaska, 2004, recorded extracellular spike activity from single neurons within the dorsal premotor cortex, DMD, of monkeys while they observed the sensory events associated with accurate performance of a saccadic motor task. They reported that when the monkeys passively observed a symbolic representation of accurate task performance, DMD neurons responded in a similar manner as when the monkeys physically performed the task. These authors were thus the first to measure mental rehearsal of a to-be-learned task occurring at the single neuron level. The studies discussed previously provide a foundation for exploring areas of overlap and divergence between observational and physical learning in the human brain. However, important questions remain concerning how physical practice compared to observational practice affects brain and behavior. To begin addressing such questions, my colleagues and I again turn to dance to determine how brain and behavior are influenced by only watching a new dance sequence, compared to physically practicing it. Cross et al. 2009. In this study, we incorporated the dance video game Stepmania, Beautiful Embodiment 195, a freeware program similar to the popular video game Dance Dance Revolution, Konami Digital Entertainment, Redwood City, CA, into our paradigm. To play this game, participants must attend to scrolling arrow cues on a computer screen that correspond to particular foot positions on a dance mat attached to the computer. When the steps are performed in quick succession with music, this approximates dancing, to some. Importantly, however, the video game context is fun, engaging, and ideal for studying motor learning, as participants receive real-time feedback about the accuracy of each movement by a points scored. In this study, we recruited 17 young adults with no formal dance training and asked them to practice 6 different dance sequences for 1 week, to observe 6 different dance sequences, and a further 6 sequences were untrained in any way. We collected scans of participants' brains with fMRI as they watched and listened to all 18 sequences before and after a 1-week training period. Following all training and scanning procedures, participants returned to the laboratory to attempt to perform all 18 dance sequences. Based on the wealth of behavioral data showing evidence for learning by observation, we hypothesized that participants' ability to perform the sequences from the observation condition would be better than their performance for the untrained sequences. This is indeed what our post-training follow-up dance test revealed. Cross et al. 2009. Of greater interest was how the brain was affected by physical compared to observational experience with the previously novel dance sequences. Importantly, in this study, participants were not instructed to try and learn during the observation blocks of the training period. Instead, they were told to just rest and watch several music videos of dance sequences they had not trained on while their heart rates recovered. Thus, they were surprised when they were asked to perform the sequences they had observed throughout the training week, as well as the untrained sequences, which were experienced only during scanning. The fMRI data revealed that physical and observational learning appeared to affect brain regions in a similar manner. Specifically, responses within the left inferior parietal lobule and right premotor cortex were quantifiably more similar when observing danced and watched sequences compared to untrained sequences. Thus, observational training, even when one might not explicitly be trying to learn, shapes responses within the aeon in a similar manner to physical practice. This was among the first brain-based evidence to suggest that mere observation of an action has the potential to build a similar neural representation of that action as physical practice. Cross et al. 2009, which added to prior behavioral support, e.g. Baydetz et al. 2006, Bandura 1986, Hodges et al. 2007, for a common neurocognitive representation of performed and perceived actions. Of course, this is not to say that observational learning is so powerful that physical practice is unnecessary for learning new motor skills. However, it does suggest that the parts of the human brain that are active during physical training might be active in a similar manner when observing others in action, and this activity appears to be related to the efficacy of learning by observation. As with the studies discussed in the first section, when examining how observation shapes action, studies using dance, as well as other highly skilled full body actions, such as 196 Emily S. Cross gymnastics and contortion, have advanced our understanding of how observation affects motor regions of the brain, e.g. Calvamarino et al. 2006, Cross et al. 2010, Cross et al. 2013, Joel et al. 2012. While some evidence suggests that visual experience alone is not enough to affect motor regions within the brain, Calvamarino et al. 2006, other research suggests that even when an individual observes movements that he or she could not possibly physically perform, extensive visual experience with these actions is associated with the emergence of neural representations within sensory motor regions. Cross et al. 2013, Joel et al. 2012. Thus, while the influence of perception on action might not be as strong as the inverse, evidence continues to accumulate to support the notion that how we see others move influences how we ourselves move. In the next section, the focus on action perception is broadened to include how we feel when we watch others move, a natural segue into the aesthetics of action. 10.4 Aesthetics of action when watching an attractive stranger dancing in a club, a solo ballerina pirouetting with ease on stage, or a street performer's breathtaking breakdancing moves, motor resonance processes are engaged. Another major factor that guides and holds our attention on the mover is how much we enjoy watching them move. When considering the aesthetics of action at either the brain or behavioral level, 2 key issues warrant discussion. The first is what, precisely, is meant by aesthetics, and the second is what kinds of entities or experiences should be eligible for aesthetic evaluation. In a forward-thinking piece on the future and utility of neuroaesthetics as a field, Brown and DeSantiaki, 2009, present a strong case for broadening the focus of aesthetics to include any perceptual phenomenon that promotes selective attention and positive emotional responses. P44. See also Oriens 2001. Consequently, they challenge the nascent field of neuroaesthetics to develop and evaluate a broader, more general conception of aesthetic responses in the brain, rather than focusing exclusively, and narrowly, on Eurocentric conceptions of art, which has typically comprised works created for a wealthy elite in the classical/fine art traditions. Brown and Desaniaki 2009. See also Brown et al. 2011. Ramachandran and Herstein 1999. One of the most prominent theoretical conceptualizations of neuroaesthetics was put forth by Freeport and Gillies, 2007. These authors argue that an important factor in shaping an observer's affective, or aesthetic, experience is the simulation of actions, emotions, and bodily sensations visible or implied in the work of art. In this theory, Freeport and Gillies, 2007, focus almost exclusively on static works of visual art in the form of paintings and sculpture, and suggest that an observer can experience embodied resonance when viewing a piece of art based on the content of the work itself or by the visible traces of the artistic medium. While a compelling case can be built to support these ideas when beholding paintings or sculpture, in many ways it seems just as intuitive and valuable to extend this concept beyond classical conceptions of visual art. Without a broader evidence base for considering aesthetic experiences, we risk underappreciating beautiful embodiment 197 the breadth and depth of aesthetic appreciation of all manner of experiences in the real world. Thus, by accepting Brown and Desaniaki's challenge that the study of neuroaesthetics should include a wide range of phenomena and experiences beyond classical paintings and sculpture, we are free to explore effective responses to all manner of objects and experiences around us, from street dance and folk music to product design and culinary creations. Along these lines, it is instructive to consider an elegant study by Hayes and colleagues that looked at aesthetic appraisals of performing or observing simple actions directed toward common, everyday objects. Hayes et al. 2008. The study of such simple actions can provide a useful template to build toward understanding effective appraisals of more complex actions, such as dance. In a set of 3 experiments, Hayes and colleagues examined how perceptual or motor fluency in terms of how an object is grasped influences participants' liking of that object. In one experiment, participants were asked to perform a fluid-reaching action to grasp an object, such as a salt shaker, or they were asked to grab the same salt shaker, but the only possible way to grab it was by performing a more awkward grasp so as to avoid an obstacle. Hayes and colleagues report that participants rated the objects with which they interacted fluidly as more likable. In a follow-up experiment, Hayes and colleagues showed participants video clips of an actor interacting fluently or awkwardly with a number of different everyday objects. They asked participants to rate how likable they found the objects based on viewing these interactions. Here again, simply the perception of a fluent grasp toward an object significantly increased participants' liking ratings. The authors conclude that fluent interactions with objects, defined in this situation by smooth, efficient movement, engender positive affect toward those objects. Hayes et al. 2008. Moreover, it does not matter whether fluent movements are performed or simply observed for the effect to manifest. Hayes and colleagues suggest that these findings are consistent with models of hedonic fluency, which posit that when a stimulus is easily processed, it is liked more. Winkleman and Cacioppo 2001. See also Berlins, 1974, Account of Perceptual Fluency. What Hayes and colleagues, 2008, added to earlier models was evidence that movement itself adheres to these same principles. In other words, objects participants attempted to grasp or watched an actor grasp with an awkward or fluid movement are susceptible to being liked more or less depending on the movement directed toward them. This evidence reported by Hayes and colleagues, 2008, fits well with Freeport and Gillies' 2007, embodied simulation notion of aesthetic processing. Perhaps unsurprisingly, since Freeport and Gillies' 2007, theoretical proposal and the behavioral work performed with simple grasping actions, a small number of research labs have begun the empirical evaluation of aesthetic responses in the human brain when watching dance. Calvo Marino et al. 2008, Cross et al. 2011, Cross and Ticini 2012, Kirsch et al. and Press. In particular, my colleagues and I have been interested in exploring the relationship between the observer's own experience and how much enjoyment they derive from watching a dancer perform. 198 MLS Cross 10.5 How action experience shapes preferences in dance spectators. The motivation for the first empirical study my colleagues and I performed that investigated neuroaesthetic responses to watching dance came from a number of sources. The first was the Skylight study that showed greater activity within the Aeon when dance experience. Participants watched movements they were highly skilled at performing. Cross et al. 2006. The second was Freeport and Gillies' 2007, embodied simulation account of neuroaesthetics, suggesting that we use our sensory-motor cortices when making aesthetic evaluations of artworks. The third and most significant motivation behind our investigation was the first study to investigate aesthetic responses of spectators when watching dance. Calvo Marino et al. 2008. In the study by Calvo Marino and colleagues, 2008, 6 dance naive spectators watched 24 movements performed by an expert ballet dancer or an expert capoeira dancer whilst undergoing fMRI. Approximately 1 year later, the investigators invited these 6 participants back to the laboratory to watch the same 24 movements. For this testing session, participants simply watched the videos on a computer screen and responded to simple questions designed to query their aesthetic experience. After Berlin 1974, the authors then used participants' group average ratings to interrogate brain regions that showed neural responses of higher magnitude when watching movements that were generally liked. They reported 2 important findings that were relevant for the follow-up study performed by my team. First, that bilateral medial visual cortices as well as right premotor cortex showed greater responses when viewing like movements. And second, that participants as a group tended to like watching whole body movements and those that involved significant displacement of the whole body across space, such as a large horizontal jump, compared to smaller or less explosive movements. Calvo Marino et al. 2008. The study by Calvo Marino and colleagues, 2008, offered an intriguing first glimpse into the neural underpinnings of an aesthetic response when watching dance. It also sparked many new questions concerning the relationship between sensory-motor brain regions and the pleasure derived from watching dance that were ripe for exploration. One main question concerned how individuals' online ratings of aesthetic value relate to brain function. In Calvo Marino and colleagues, 2008, paradigm, all 6 participants' aesthetic ratings were averaged into one value for each dance movement, and aesthetic ratings were collated in a later testing session outside the fMRI scanner. Thus, this paradigm did not allow the authors to address individual differences in aesthetic preferences the first time the movements were watched. In our study, we wished to address these specific issues of individual differences in aesthetic preferences, as well as how an observer's physical ability to perform a movement interacts with their enjoyment of watching a movement. Cross et al. 2011. In our experiment, participants' main task was to rate 64 3-second video clips of dance movements performed by either a male or female professional ballet dancer. When we were filming the 2 dancers to construct the stimuli, we asked them to perform a range of beautiful embodiment 199 movements from both classical ballet and contemporary dance vocabularies, and to vary the size, intensity, and complexity of the movements, so that we ended up with the widest possible range of different movements. We then piloted 100 video clips on several dozen participants, who did not take part in the main experiment, whom we asked to rate each movement on how difficult they thought it would be to reproduce, as well as how much they liked watching it. From these pilot ratings, we selected the 64 dance clips that elicited the broadest range of ratings in terms of both liking and reproducibility. For the main experiment, we recruited a study sample of 22 dance naive participants who underwent fMRI scanning while watching the dance video stimuli and answering one question after each video clip. The question was either how much did you enjoy watching the previous video, or how well do you think you could reproduce the previous movement. Participants responded to each question according to a 1 to 4 response scale, with 1 corresponding to liked it a lot or could perfectly reproduce the movement and 4 corresponding to did not like it at all or could not reproduce the movement at all. To understand the relationship between embodiment and aesthetics within our study design, we assessed what the behavioral data revealed in terms of the relationship between liking and reproducibility ratings, as well as what the brain imaging data revealed about how the action observation network responded to movements that could be physically reproduced compared to those that were pleasing to watch. If our data were to support dominant theories of the Aeon, which state these brain regions respond most to movements that a participant can perform or are present in their action repertoire, e.g. Calvo Marino et al. 2005, Cross et al. 2006, then we would predict most Aeon activation when watching the movements that participants rated as easily reproducible, independent of aesthetic value. However, if the embodied simulation theory of aesthetics more accurately explains how our brains respond to aesthetically pleasing stimuli. Friedberg and Gillies 2007. Then we would predict strongest Aeon activity when watching movements that participants ranked as most pleasing, independent of how possible it is to reproduce them. The results yielded several interesting and surprising findings. First, we found a strong negative relationship between enjoyment and perceived ability to physically reproduce a movement. Figure 10.2a. This analysis demonstrates that in our study, liking and physical ability ratings were not independent, as participants showed a tendency to prefer those movements that they rated as extremely difficult to reproduce. As far as the fMRI data were concerned, we chose to apply a series of parametric analyses to our data, which enabled us to look at participants' individual liking and reproducibility ratings for each stimulus, and query how brain responses change as movements are rated as increasingly, or decreasingly, likable or increasingly, or decreasingly, easy to reproduce. We found that several regions within the Aeon, specifically occipitotemporal cortex and the inferior parietal lobule, show increasingly strong activation the more movement is liked. Curiously, when we asked which brain regions show greater activity the more easily a movement is reproduced, we failed to replicate the findings from our previous study with 200 MLS cross-expert dancers, cross-ETAL 2006. Our 2006 study demonstrated greater parietal and premotor engagement when expert dancers rated movements as increasingly possible to reproduce. In our 2011 study with non-dancers, no brain regions emerged from a contrast evaluating brain areas showing increased activity the better an observer is at performing an observed action. When we evaluated the inverse contrast, designed to reveal brain regions showing stronger activity the more difficult a movement appears, activity emerged within bilateral visual cortices. Figure 10.2b illustrates the overlap between these two analyses within the occipital cortices of the brain. The most interesting analysis in our view, however, directly compared the interaction between liking and perceived physical ability. Put another way, this analysis asked which brain regions respond more strongly when participants watch a movement they really like, but which they also judge to be extremely difficult to reproduce. As with this simple parametric analysis of liking only, here we saw robust activation of bilateral occipitotemporal cortices, as well as the red inferior parietal lobule. Thus, it appears that watching exciting, or enjoyable, movements that would be impossible or extremely difficult to perform engages certain portions of the Aeon that are implicated in action embodiment. Cf. Calvamarino ETAL 2005, Cross ETAL 2006. When the behavioral and imaging findings are considered together, they appear somewhat contradictory to the findings reported by Hayes and colleagues, 2008, and what might be predicted by the perceptual or hedonic fluency accounts of stimulus processing, Berlin 1974, Winkleman and Cacioppo 2001. One reading of what these accounts would predict is that participants should find less pleasing those movements that would be extremely difficult for them to perform. However, it seems that the perception trumps actionability when dance-naive participants watch dance movements for the first time, and seeing a dancer perform a highly complex movement with apparent ease and grace is extremely enjoyable, even if, or even especially because, a participant could not come close to achieving the same thing with his or her own body. This explanation finds much anecdotal support, of course, when considering that people pay large sums to money to see physical feats that most of us could never perform ourselves, such as the incredible precision of dancers in the Forsyth Company, the acrobats in Cirque du Soleil, the slam-dunking professional basketball players in the NBA, or the action hero who narrowly escapes death by leaping across rooftops of burning buildings and jumping to safety on a passing helicopter. What we discuss in our paper is that watching an aesthetically pleasing movement might drive activity within certain parts of the Aeon because interest in the movement drives sensorimotor regions to work harder to try and embody the movement. Cross ETAL 2011. As such, we argue our findings lend tentative support to Friedberg and Gillies' 2007 proposal that a perceiver's use of his or her own body to simulate what is seen in an artwork, or any stimulus, is related to his or her aesthetic experience of that work. Of course, this relationship between lack of physical ability, favorable aesthetic evaluation, and Aeon activity reflecting an increased drive to embody a movement remains beautiful embodiment 201 speculative at this stage, and it will require careful empirical evaluation. Moreover, my team's 2011 study is not without shortcomings. One major limitation to this study is that we relied on participants' self-report of physical ability to reproduce movements, instead of actually asking them to attempt to perform each movement they watched. Point 1 is a next step toward understanding how physical experience is related to aesthetic evaluation. Work in my laboratory is underway to test how learning to perform a dance sequence affects participants' aesthetic appraisal of it. In one experiment, we implemented a between subjects training design with 60 dance-naive participants. Our question was whether aesthetic ratings of a dance sequence increase or decrease as a participant learns to perform that sequence. Because actual physical ability was assessed, we again chose to use a video game paradigm that evaluates dance performance in an unbiased manner. However, we have taken a step forward in the complexity of movement scoring by using the Xbox Kinect trademark system in conjunction with the Dance Central 2 video game. This system uses sophisticated whole-body motion tracking and relays real-time feedback to participants as they dance along with an avatar on the monitor. In this behavioral study, participants were split into 3 groups of 20. They came into the laboratory across 5 consecutive days for training, and took part in a pre-training rating assessment before the first training session and a post-training rating assessment after the last training session. Among the 3 training groups, one group physically practiced several routines of hip-hop/dance club movements choreographed to a popular song. A second group just watched the avatar dance to same sequences while also listening to the music, and a third group only listened to the music from the dance sequences in each training session. Contrary to what we found when dance-naive participants watched professional ballet dancers perform short dance sequences, the data from this between subjects behavioral training study suggests that participants who physically practice a dance sequence across a week of training show significant increases in their aesthetic ratings of the dance movements on several dimensions. Notably, just watching the sequences and listening to the corresponding music, or just listening to the music alone did not correspond with an increase in enjoyment of any dimensions of the dance sequences, so we can be fairly confident that it is not a mere exposure or familiarity effect in the audio or visual domains. Rather, it appears physical performance of these particular dance sequences contributes to positive aesthetic appraisals. Data from our most recent training study, which implemented the dance training procedures described for Kirsch and colleagues, 2013, and added pre- and post-training fMRI measures, replicate the behavioral effects described by Kirsch and colleagues, 2013. Moreover, these latest neuroimaging data provide evidence for a shift in neural engagement from subcortical regions associated with dopaminergic reward processing when observed movements are novel to cortical regions associated with multisensory integration and higher-level emotional processing once dance movements have been rehearsed. In terms of what might explain the contradictory findings between our fMRI investigation with novice dancers watching professional ballet dancers, Cross ETAL 2011, and our latest training studies with novice dancers learning to perform hip-hop/street dance moves in a video game context, Kirsch ETAL 2013, in press, we suggest that there are likely to be multiple ways in which embodiment and aesthetic preferences interact. One possibility is that a U-shaped function, similar to the one we proposed in a related study on action familiarity, Cross ETAL 2012, might partially explain why we derive intense pleasure from watching movement that is familiar, practiced, and well within our physical capabilities, as well as movements that are so spectacular and novel and far beyond our ability to reproduce them. Returning to the flash mob example discussed at the start of the chapter, I propose that the reason dancing flash mobs are so effective in engaging and delighting onlookers is because they satisfy both possibilities, thus resulting in maximum enjoyment. First, flash mobs feature dancers that look like all other pedestrians in the crowded public space in which they materialize, and onlookers can easily imagine dropping their own shopping bags and joining in, if only they knew the choreography. Second, dancing flash mobs elevate the common pedestrian to the exalted status of a dancer who is extremely adept at performing a sequence of movements that are often highly complex and have required hours of practice. Point 2 Thus, the appeal of flash mobs might lie in the fact that they are made up of individuals who look much like the onlookers, and yet move in a complex, coordinated way that invites others to dance along, even if they do not know the moves. 10.6 Next steps in using dance to explore embodiment and aesthetics. The overarching aim of this chapter has been to highlight 2 areas where the convergence of dance and neuroscience has the potential to further our understanding of the human brain. The first is that action perception and production share common neural substrates, and dance provides a useful means for exploring this relationship. The second is that notions of embodiment and an observer's prior sensorimotor experience might help to illuminate the parameters guiding why and when we derive pleasure from watching others move. As has now been suggested by a number of researchers with expertise that spans the dance and neuroscience domains, ongoing collaboration between the dance and scientific communities stands to benefit both disciplines. Blazing ETAL 2010, 2012, Cross 2010, Cross and Ticini 2012, Hagendorn 2004, 2010, Jola 2010, Borgs ETAL and Press. While most of the work described in this chapter has used dancers as participants or dance learning/perception as a paradigm for studying full body movement without much concern for the artistic properties of dance per se, the field of neuroaesthetics is one where science has the potential to benefit the dance world, depending, of course, on the right questions being asked. Along these lines, one platform that is encouraging collaborations between scientists and dancers from the Foresight Company is the Dance Beautiful Embodiment 203.11224433. 1. Premotor cortex action observation network. 2. Inferior parietal lobule. 3. Occipitotemporal cortex. 4. Supplementary motor area figure 10.1 schematic of the action observation network. The action observation network is distributed bilaterally and comprises brain regions active when watching other people's bodies in motion. The core regions of this network are 1. The ventral and dorsal premotor cortices. 2. The inferior parietal lobule, often extending posteriorly along the interparietal sulcus. 3. More anterior portions of the occipitotemporal cortex, including posterior superior temporal sulcus as well as the lateral occipital complex. And 4. The supplementary and pre-supplementary cortices located on the medial surface of each hemisphere. The particular set of brain regions illustrated here came from a contrast that compared watching dancers in motion compared to dancers standing still. Figure is originally published in Emily S. Cross, Louise Kirsch, Luca F. Ticini, and Simone Kutzbosbach, 2011. The Impact of Aesthetic Evaluation and Physical Ability on Dance Perception, Frontiers in Human Neuroscience, 5, Figure 2 doi, 10.3389/1.2011.0012. Engaging Science Interdisciplinary Research Workshop Series. As a consequence of this series, a number of exciting new collaborations focused on how the neuroscience of action and perception relates to movement aesthetics are being forged with equal input from dancers and scientists, e.g. Waterhouse ETAL 2014. While such interdisciplinary work necessarily faces myriad challenges of accommodating different vocabularies, priorities, and goals, it also sets us on a path worth exploring, and will hopefully further elucidate the links between the embodiment and enjoyment when watching or performing dance. Chapter 11 Sensorimotor Aesthetics, Neural Correlates of Aesthetic Perception of Dance. Beatrice Calvo Marino 11.1 Do we need a neuroaesthetics of dance? The study of neuroaesthetics has expanded in the last decade, and with the use of cognitive neuroscience techniques, such as functional magnetic resonance imaging, fMRI, or magnetoencephalography, MEG, this recent work has aimed at elucidating the neural underpinnings of aesthetic experience. Many of these studies have focused on the aesthetic perception of beautiful compared to less beautiful artworks, classified according to individual preference, revealing some neural mechanisms for the visual perception of pleasant stimuli, or for aesthetic judgment itself. Selakonda ETAL 2004, Jacobson ETAL 2006, Kawabata and Siki 2004. Alongside studying the reception of paintings and sculptures as artworks, Didio ETAL 2007, a smaller proportion of research has studied the aesthetic perception and neural underpinnings of music, Blood and Zederer 2001, Petrini ETAL 2011. By and large, this work is based on our in-depth knowledge about visual perception, auditory processing, or decision-making. For an extended review on neuroaesthetics of artwork and music studies, see other chapters in this volume. Didio and Galiz 2009, Nadal ETAL 2008. Another large body of work in the cognitive neurosciences investigates the neural basis of movement processing, with a growing number of studies investigating the role of human actions in the human body. Generov 1997, For Social Interactions, Johnson and Schifrar 2013. This research has set the necessary neurocognitive grounds to start exploring the processing of a different form of art, the performing arts. The idea of a neuroaesthetics of performing arts, and dance in particular, has won a dedicated following in the recent neuroaesthetic literature. To date, a few studies have focused on understanding the neural processes associated with watching and enjoying dance. One may wonder if the study of the neural correlates of the aesthetic experience of performing arts, or dance in particular, is any different from the neuroaesthetic studies of any other type of art, such as painting, sculpture, or music, and therefore whether the neuroaesthetics of dance demands a special role in this type of research. This chapter, and chapters 10 and 12, provide a series of arguments as to why it should. Here, we will revise the current knowledge about the neural mechanisms associated with the aesthetic 210 Beatrice Calvo Marino perception of dance, and evaluate avenues for future research. We will describe 3 reasons that justify the consolidation of the neuroaesthetics of dance as a special discipline within the broader umbrella of neuroaesthetics. The 2 following chapters will focus on 2 very important issues that relate to the aesthetic appreciation of dance. 1. The specific effect of dance experience and familiarity during aesthetic perception of dance, Chapter 10, and 2. The evolution of dance research towards a more ecological approach to investigate aesthetic experience in performing arts, Chapter 13. 11.2 The body is a dynamic human canvas. The first, simplest, and yet fundamental differences between dance and other kinds of art is that in dance, both the artist and the artwork are contained within the human body. The body itself, or to be more precise, the dancer's body, acts as a kind of dynamic canvas from which dance movements flow. The spectator of a dance performance is visually exposed to intertwined bodies and movements. From a neuroscientific perspective, the mere observation of such a scene engages specific brain mechanisms that process information about bodily movements. The underlying brain regions processing this information are significantly different from those associated with static visual stimuli, such as objects, or auditory information, music. Understanding the specific neural mechanisms for the processing of bodily movements therefore provides a starting point for many of the experimental studies that will be presented here and in the following chapters. We start with a brief introduction about what is currently known about the processing of bodily movements. 1.2.1 Specific brain mechanism for observing bodily movements. Neuroscience has shown that biologically relevant stimuli such as faces and bodies are processed in a different way to other non-biological stimuli, i.e. objects. At the neural level, one specific brain region, the fusiform face area, FFA, has been found to respond specifically to the perception of human faces, Kanwisher ETAL 1997. It is posited that a similarly specialized brain region participates during processing of human bodies. Experiments using fMRI have identified 2 body-specific brain regions. The first region was found in the lateral occipitotemporal part of the human brain. This area has been labeled the extrastriate body area, EBA, Downing ETAL 2001, and it responds to the observation of human bodies or body parts, arms, legs, etc., as well as to the observation of bodies depicted in photographs, drawings, or movies, Phelan and Downing 2005. A second body selective area was recently located in the fusiform gyrus, very close to where the FFA has been located. This region is known as the fusiform body area, FBA, Phelan and Downing 2005, and it responds to the observation of whole bodies and body parts. These 2 body areas seem to have separate functions during body processing. For example, while the EBA responds to simple presentation of bodies and body parts, the FFA is largely activated during the presentation of complex body configurations, rather than a simple body part, i.e. an arm, Taylor ETAL 2007. Sensorimotor Aesthetics 211 This neural specificity for faces and human bodies is also accompanied by a particular perceptual way of seeing. 2 types of visual mechanisms have been described in perception, configural and analytical processing. While the perceptual process of objects involves an analytical perception of the different parts composing the object, the perception of faces and bodies triggers a more configural way of seeing, Valentine 1988, Reed ETAL 2003. In the latter, the stimulus is processed as a whole, providing a holistic perception of the observed stimuli from a very early visual stage, Moore ETAL 2002. Configural processing has been interpreted as a more efficient and fluent machinery for understanding external events. Research has concluded that this special processing scheme may have appeared during evolution due to the importance of faces and bodies in life, and the high level of visual exposure that we have acquired over our evolutionary history. 1.2.2 Specific brain mechanisms to watch the dynamic human body. Only through movement can humans interact with the world. It is through movement that we are able to communicate with others, express our emotions, and interact with external objects. The performing arts, and dance in particular, have made this particular human feature their essential tool. Dance is dynamic and involves the displacement of a human body in time and space. As a consequence, dance observation may recruit a particular neural mechanism involved in movement processing that is qualitatively different from processes involved in merely watching static objects. Traditionally, movement research has been concerned with the neural foundations of movement execution and motor control. Gene-Rod 1997. Each acquired movement is internally represented in our own neural and cognitive system in the form of motor representations. Recent research has focused on the internal components of such representations rather than the overt movement. These representations play an important role during action execution, but interestingly for our discussion, also during action observation, movement understanding, and as we will see later, aesthetic perception of movement. To summarize some of this work, let us look into Giacomo Rizzolatti's laboratory in Parma University in the early 1990s. In a series of studies using cell recoding in primates, his team discovered a group of neurons in the ventral premotor cortex, VPMC, of a primate that spiked in a similar fashion when a monkey was making a movement, and when the animal was merely observing the experimenter performing the same action. De Pellegrino et al. 1992, Rizzolatti et al. 1996. These neurophysiological studies marked a turning point in the field because they described for the first time a common coding mechanism for executed and observed actions. Similar results were found in other areas in the primate brain, such as the parietal cortex, Galete et al. 1996, see Rizzolatti and Craig Bureau 2004 for a review. Collectively, this work suggests that the motor system is recruited in a similar manner during both motor execution and the observation of movements. Movement representations thus appear to store motor properties and information associated with acquired movements that we have learned to perform, and provide an entree to internal motor knowledge just by 212 Beatrice Calvamarino action observation. In other words, we can see other people's movement with our own movement repertoire. Neurons with these visual and motor properties were called mirror neurons, as they seem to reflect, like a mirror, observed actions as much as actions from our own motor repertoire. The first evidence for coexisting action observation and action execution systems in the human brain came from a transcranial magnetic stimulation, DMS, study performed by Fadivet and colleagues, 1995. These authors reported similar muscle excitability patterns during execution and observation of the same action. This is a fascinating result that illustrates how the muscles from the physical effectors involved in an action, i.e. arm and hand during the grasping movement, are also activated in a similar manner when we observe someone else performing that same action, i.e. when we observe someone else grasping. This study and subsequent work, Stratola and Paus 2000, Baldisera et al. 2001, have provided increasing evidence for internal motor resonance in the human brain. Consistent with the original work in non-human primates, human fMRI studies have sought to identify brain regions that participate in both action execution and action observation. Brain activation during action observation has consistently been reported in ventral and dorsal premotor cortex, VPM, DPM, areas in the parietal cortices, such as the inferior parietal lobe, IPL, and superior parietal lobe, SPL, and superior temporal sulcus, STS, Dicity et al. 1997, Grafton et al. 1996, Iacoboni et al. 2001, Rizzolatti et al. 2001. From these regions, the premotor and parietal cortex have well-defined functions during action execution, and may represent the core of the so-called human mirror neuron system that links action execution and action observation. The STS responds to action observation, but this area does not assume any motor functions and therefore, strictly speaking, does not fall into the category of mirror region. However, the STS may be part of a general action observation system that goes beyond mirror neuron regions, because it responds to visual and non-visual presentation of other type of social stimuli. Allison et al. 2000, Fuse and Perret 2003. Finally, some other areas that are classically identified during action execution, such as the supplementary motor area and primary motor cortex, are normally not activated during action observation, unless there is a motor preparation element involved. For example, if the task includes a subsequent motor imitation. Breezes and Dicity 2001. For a more detailed overview of the human mirror neuron system, see Rizzolatti and Sinigaglia, 2010. Finally, cognitive psychology has also explored whether movement processing engages a series of specific mechanisms similar to the ones described for faces in human bodies. Several studies have shown that recognizing the performing agent, his/her gender, or identifying the action may require a kind of global or configural process of the movement. Mather and Murdoch 1994, Troche 2002. This configural process is particularly engaged when observing familiar actions. Calvamarino et al. 2010. Recognizing other action features such as the emotion represented in a movement can use more analytical or visual analysis. Pollock et al. 2001. Although other studies have shown that a similar task of reading emotion can be performed using only configural information. Dittrich et al. 1996. Sensorimotor Aesthetics 213 overall. This series of studies sheds light on several neurocognitive processes for body and movement observation that should be taken into account when investigating the aesthetic appreciation of dance. 1.2.3 The dancer's body. A human gem. A second though no less important issue to consider when investigating the neuroaesthetics of dance is the special quality of a dancer's body. The physical training entailed in learning this art makes dancers unique by affording them a set of movements that far exceeds the type of movements our body articulations normally allow. Dancers' flexibility and smoothness during movement execution is not comparable to the motor ability of any of the rest of us. Dancers' bodies are special, and this is reflected not only in their physical bodies and how they move, but also in some of their cognitive abilities. Blazing et al. 2012, ranging from basic motor control mechanisms including equilibrium, posture, and complex movement execution, to the sense of timing, motor memory, motor imagery, or spatial transformations. Here, we will briefly describe how dancers' acquired motor skills influence the way action and movements are processed. The first imaging study describing an expertise effect during action observation compared brain activity of different types of motor experts, i.e. ballet dancers and capoeists, when observing familiar and non-familiar movements. Calvamarino et al. 2005. Both groups observed a number of 3-second video clips of standard ballet dance and capoeira movements. These movements were performed by professional dancers dressed in black garments in front of a blue background. The dancers' faces were blurred. These last observations are important as the study aimed to isolate brain activity related to the observation of movements, whilst controlling for other elements often associated to a dance performance such as costumes, choreography, music, or facial expression. This study demonstrated different brain activations when dancers were observing dance movements that were familiar to them, ballet dancers watching ballet movements, and capoeists watching capoeira movements, see Chapter 10, compared to watching unfamiliar movements, ballet dancers watching capoeira movements, and capoeists watching ballet movements. Observation of familiar movements elicited stronger brain responses in the bilateral premotor, ventral and dorsal regions, parietal cortex, bilateral interparietal sulcus, and right superior parietal cortex, and left posterior superior temporal sulcus, PSTS. These results are interesting because premotor and parietal regions have been included as part of a mirror neuron system. This suggests that if we observe an action we are familiar with, and therefore an action that is part of our motor repertoire, we automatically enhance the response of the corresponding motor representations when we merely watch that action. In general, the information content in these motor representations may be used during observation of that action and may help understand the meaning of this action, predict its output, and plan a complementary response. Interestingly, other areas, such as the PSTS, also responded more strongly when observing familiar movements, suggesting a complementary response associated with expertise outside the Mirror 214 Beatrice Calvo-Marino mechanism, but also in areas associated with visual body and human processing, Calvo-Marino ETAL 2005. This latter result triggered new experiments that sought to clarify how much of this effect during observation of familiar movements is due to motor familiarity, having acquired the observed movement in our motor repertoire, or whether visual experience alone can explain these results, i.e. strong or prolonged visual exposure to the observed action, without having physically trained them. To disentangle this question, we developed an fMRI study that allowed isolation of motor response from visual responses, Calvo-Marino ETAL 2006. With the help of choreographer Tom Sapsford, 4 sets of stimuli were created. The first 2 involved a male and a female dancer performing gender-specific ballet movements, whilst the other 2 involved a male and female dancer performing common ballet movements. It is important to note that classical ballet movements are well categorized. For example, some movements are gender-specific and are therefore only performed by either male or female dancers. However, because both males and females train together, they both have extended visual familiarity with all the dance movements. In the experiment, male and female dancers therefore performed together a series of common movements with whom all dancers had extensive visual and motor training. The comparison between females and males watching a gender-specific movement and using the common movements to control for gender differences while observing, then allowed for the identification of the specific brain responses associated only with motor familiarity. This comparison revealed stronger brain activations in premotor and parietal cortices, the classical mirror neurons regions. This study thus provided some of the first evidence for internal motor resonance during action observation. The study cited above made use of professional dancers in order to understand a question initiated in the cognitive neuroscience domain. They also showed that dancers' brain responses in some mirror neuron regions are stronger than the brain responses in non-dancers. These results demonstrate that the physical abilities of professional dancers provide them with a unique repertoire of movements that influence how they can observe and see actions, including actions that untrained individuals would find difficult to perform or to understand. Other studies using dancers have shown similar results, Cross ETAL 2006, Sports ETAL 2008. Finally, it is important to note that the key comparison here is about the differences in brain activation between dancers and non-dancers. This marked difference does not imply that non-dancers do not have the ability for action observation, but it does suggest that the resonance is larger when we are familiar with the observed movement. Besides differential neural responses during observation of dance movements, dancers' motor skills have also been shown to influence responses at the behavioral level. For example, in a similar expertise paradigm to the one described earlier, dancers showed better visual discrimination of familiar dance movements than non-dancers, Calvo-Marino ETAL 2010. This suggests that the expertise effect that surrounds dancers, due to their exquisite motor skills, during action observation is observable at the neural and at the behavioral sensory motor aesthetics 215 level. A further description of expertise modulations and how they are related to the aesthetic processing of dance is described in the preceding chapter. 11.2.4 The spectator's body, mirror. Despite the extraordinary motor abilities of dancers, their body configural features remain similar to those of non-trained bodies. Human bodies of dancers and spectators, non-dancers, share the same structure, i.e. body parts, head, and limbs, organized in a specific configuration. This similarity evokes a unique relationship between the observer and the dancer, who is himself the artwork, at the sensory motor or embodiment level. Who has not closed their eyes or felt goosebumps when watching the beginning of Dali's film Paramandalas, or a dramatic painting representing a human in pain. When these physical human body features are depicted in art, they are often experienced viscerally. Freeport and Dali's 2007. The previous sections have described the neural basis of experiencing our own and other people's body/movements in the context of action perception. This self-other matching mechanism, or mirror neuron mechanism, has been generalized to other aspects of social perception, such understanding of others' emotions, feeling empathy, Dali's 2005, de Vignemont and Singer 2006, and, potentially, aesthetic perception. 11.3 Neural correlates of aesthetics experience of dance is a type of performing art. Dance is intrinsically linked to the concept of the aesthetic. However, how is the human brain aware that dance may warrant an aesthetic response? Is there an ongoing aesthetic response every time we observe a dance performance? Or is there only a specific response when we tune in our aesthetic senses during the dance observation? These and other questions arise when we study any behavior associated with aesthetics in general. Here we aim to provide some answers, but it is worth noting that the field of the neural aesthetics of dance is quite new, and the complex relationships between the observer/spectator, the dancer, the movement, and associated aesthetic processes offer a rich scene for the curious researcher. 11.3.1 Implicit neural aesthetics of dance. The first study to focus on the neural correlates of implicit appreciation of dance sought to define brain responses that correlated with the level of implicit liking towards the observed dance movement, Calvo-Marino ETAL 2008. The experiment was divided in 2 parts. The first session measured brain responses associated with the visual process of watching a series of dance movements comprising a variety of kinetic properties, speed, dance style, amount of displacement. In a second session, individual preferences of those movements were obtained. This enabled exploring how neural responses to observed movements related to the preference or liking of these movements. More specifically, during the fMRI session, brain activations were measured from participants without any dance experience whilst watching dance movements from 2 different disciplines, Classical 216 Beatrice Calvo-Marino Ballet and Capoeira. The participants were asked to look at the dance movements and indicate how tiring they judged each of the movements to be. Importantly, during this session, there was no question or reference to the potential aesthetic quality of the movements. In a second session outside the scanner, participants were asked to explicitly rate all dance movements across several dimensions related to aesthetics experience. 5 dichotomous scales were used: liking, disliking, simple, complex, interesting, dull, tense, relax, weak, powerful, early 1974. From this set of ratings, only the liking-disliking dimension correlated with brain activity changes. To explore the meaning of these activations, further analyses were performed. Dance movements were divided into 2 sets. One set contained the movements with the highest scores across the group of participants, and the other those with the lowest scores. This permitted identifying brain areas that were sensitive to this categorization. This analysis showed 2 regions that were sensitive to generally appealing and well-liked movements. These aesthetic-sensitive areas were localized in the early visual cortex, in the medial region precuneus, and in the premotor cortex of the right hemisphere. The opposite comparison showed no significant results, i.e. when looking for brain regions sensitive to viewing less like rather than like movements. This finding indicates the existence of an automatic sensory-motor brain mechanism concerned with the observation of positive appreciation of dance movements. In particular, sensory-motor responses may be stronger when we see dance movements that we implicitly like, Calvo-Marino ETAL 2008. 11.3.2 Explicit neuroaesthetics of dance. Recent work has extended this finding and investigated the brain activity changes associated with making an explicit aesthetic judgment about a dance movement, Cross ETAL 2011. In this study, participants' brain responses were measured while they observed a series of dance movements. After each observation, participants were instructed to rate how much they liked each individual dance movement, or how well they could reproduce it. We will discuss this part of task later. The authors focused on brain regions that are known to respond to movement as compared to other features such as the dancer's body or costume. Their results showed that activation in the right parietal cortex, inferior parietal lobe (IPL), and occipitotemporal cortices, namely motion area V5 (MT), and body regions in inferior temporal gyrus (ITG) and middle temporal gyrus (MTG), correlated positively with the degree of liking. In other words, the higher the liking ratings for any particular movement, the stronger were the neural responses in these brain regions. For a detailed description of this study, please see Chapter 10, this volume. The causal or correlational role of classical movement, premotor, and body areas (EBA) was investigated in a TMS study. Calvo-Marino and colleagues, 2010, presented pairs of dance postures to participants with no dance experience who were asked to indicate which of 2 dance postures they liked more. Scrambled versions of the same body posture were used as control stimuli. Results demonstrated that repetitive DMS, RTMS, over the EBA region blended aesthetic judgments about body postures relative to ventral PMC sensorimotor aesthetics, thus disrupting the pattern of aesthetic preference observed for each participant in a rating session without stimulation. This shows that both EBA and the premotor cortex contribute in a complementary manner to body aesthetic evaluation. Interestingly, we interpreted these results within the framework of the dual root model of visual body perception, Urgency ETAL 2007, suggesting that disruption of the local system, housed in the EBA region, blunted the aesthetic sensitivity. To the opposite, the disruption of the ventral premotor cortex, involved in the configural processing of whole body postures, heightened aesthetic sensitivity. 1.3.3 Sensorimotor aesthetics of dance. The available studies on neuroaesthetics of dance show that a combination of implicit and explicit aesthetic perception of dance movements activates a set of regions that involve the premotor cortex, in the dorsal region, parietal cortex, IPL, and occipitotemporal region, V5, MT, ITG, MTG, precuneus, Calvo-Marino ETAL 2008, Cross ETAL 2011. These regions have one function in common: they all are activated during action observation. The premotor and parietal regions are part of the mirror neuron system and thus have a shared mechanism for both executing and seeing movements that could represent the neural links between the observed agent and the observer. Occipitotemporal regions have also been frequently observed during action observation and body perception. Interestingly, these areas do not have visuomotor properties, as is the case of premotor and parietal cortices. They are, however, part of a network of regions involved in body processing that seems to have been biologically tuned to respond to particular components of the human figure, Urgency ETAL 2007. A broader neuroaesthetics perspective describes how the organization of artworks may reflect the properties of the human visual system, CP 1999. In the specific case of performing arts, the few studies that have explored the topic suggest a strong relationship between the sensory process involved in perceiving the dance movement and the associated positive aesthetic response. It is important to notice that both the studies by the teams led by Calvo-Marino and Cross found a number of brain regions in which activity was related to the degree of legging of observed actions. In other words, higher legging ratings correlate with stronger brain response in the corresponding sensorimotor regions. However, both studies failed to find brain regions in which activity related to the degree of disliking. This suggests that while we know that some brain regions are sensitive to the level of positive legging during movement perception, more research is needed to clarify the brain regions tuned when we observe dance movements that we dislike, or more accurately, have received lower ratings in the legging scale. 11.4 Neural correlates of dance's physical properties. Most studies conducted up until now have followed an individual or subjective approach that aim to understand the brain responses correlating with preference behavior, regardless of what has been the output of that preference. This research focuses on the individual's 218 Beatrice Calvo-Marino brain, not on his choices. However, in the neuroaesthetic of dance, there is a growing keenness to understand the relation between the dance itself, the movement, and the associated aesthetic response. In one of our previous studies, Calvo-Marino ETAL 2008, a first attempt to identify kinematic properties intrinsically linked to neural processes which are linked to aesthetic experience, movements were selected on the basis of four kinematic properties: speed, body part used, direction of movement, and vertical and horizontal displacement. In the analysis, we eliminated differences between individuals when generating a group average or consensus of like versus less like movements. This permitted the identification of stimulus quantities that specifically modulated activity related to those aesthetically sensitive brain areas of that group of participants. In this way, we identified which specific dance movements were responsible for maximal and minimal activation for the two aesthetically sensitive brain regions previously described, dorsal premotor and occipital cortices. The results suggested that on average, these areas preferred whole body movements, such as jumping in place, or with a significant displacement of the entire body in space, e.g. horizontal jumps. At the behavioral level, a similar type of analysis suggests that the kinematic properties of the movements that receive the highest and lowest consensus on the legging score in the subjective rating show clear correspondence with the movements that target the brain areas revealed as aesthetically relevant in the functional imaging analysis. Overall, these results suggest a high level of correspondence between some dynamic properties of the dance movements: speed, high vertical and horizontal displacement jumps, a positive legging behavior, and the maximal activations in the above-mentioned aesthetic sensitive regions. Another movement parameter that has often been associated with the idea of dance as a domain for motor experts is the level of difficulty associated with performing the movement. Dancers have the extraordinary ability to perform extremely challenging movements in an effortless manner, and the non-trained observer often uses his or her judgment about the difficulty level during their aesthetic judgment. Perceived motor difficulty can also be described as the observer's evaluation on how well he or she could possibly perform the observed movements. Following this idea, Cross and colleagues, 2011, asked about aesthetic experience during the fMRI session, and participants rated how well they thought they could reproduce the observed movement. While no significant activations were found in the action observation network, the behavioral data indicated that legging and perceived physical or motor ability ratings were not entirely independent. In other words, those dance movements that they rated as difficult to perform were liked by participants more. The idea behind this research opens a line of correspondence between neuroaesthetic research and dance. This can help to explore still further the relationship between aesthetic sensitivity, or in this case, neuroaesthetic sensitivity, and movement kinematics. Despite the different methodologies used by Calvo-Marino and colleagues, 2008, and Cross and her team, 2011, and the lack of opportunity for the direct comparison between studies, we could speculate that the physical movement descriptions of our study may also correspond to those that participants would have rated as more difficult to perform in the study by Cross and colleagues, 2011. Having said that, it is interesting to note that while our study revealed aesthetically sensitive areas that correlated with the legging dimension, the study did not reveal significant brain activity changes related to other aesthetic components or dimensions described in Berlin, 1974, such as complexity or symmetry. Legging was the only dimension that evoked a significant aesthetic response. However, the complexity of the stimuli, or the perceived complexity, can be closely interpreted by observers as a feature to guide their interpretation of how well they think they could perform such movement. Further studies are needed to explore these matters and the relation between physical and aesthetic dimensions and the kinematic features associated with them. 11.5 Future directions. This chapter sought to provide a brief introduction to the neural mechanisms that participate during the aesthetic experience of dance perception. The direct correspondence between the observer's body and the performing dancers permits the consideration of the neuroaesthetics of dance from a sensorimotor or bodily perspective. This suggests that there is an ongoing internal representation of the dancer's body and movements in the spectator's mind while he or she watches a dance performance. This simulation may be passive, but at a certain level it influences the final aesthetic judgment made of the observed dance piece. The judgment is also modulated by a large number of factors that have not been described here. Chapter 10 and Chapter 12 focus on understanding A. How experience and familiarity participate in the aesthetic experience of dance, and B. How research can be carried out on dance aesthetics beyond the simple body and movement embodiment approach, including essential features for an ecological dance experience. Chapter 12 Moving towards ecological validity and empirical aesthetics of dance. Julia F. Christensen and Corinne Jola, both authors, contributed to the chapter equally. 12.1 Far from ecological validity. 2.1.1 Positioning dance in experimental neuroaesthetics. In order to conduct experimental research on the effects aesthetic objects can have on its recipients, empirical psychologists accept the reality of aesthetic experiences. An aesthetic experience then has been described as a mental state, e.g. Goulart and River 2013, Schusterman and Tomlin 2008, or a composition of psychological processes, e.g. Letter ETAL 2004, evoked within a spectator through his or her perception of an object located in the external world. Often, but not exclusively, such an object can be a work of art. Notably, in psychology, the aesthetic responses to visual art have been studied for over a century. This approach has its roots in psychophysics, although in recent years aesthetic appreciation has also been approached from the perspective of cognitive neurosciences, giving rise to the field of neuroaesthetics, CP 1999. Across all these domains, neuroaesthetics, experimental aesthetics, philosophy, the study of aesthetic experience in response to watching dance is still limited by a focus on the features derived from visual artifacts as the determinants of aesthetic value. This chapter seeks to pave the way to a more thorough discourse of aesthetic experience in the field of dance. In order to achieve this, we aim to acknowledge three dimensions that have been found to be particularly relevant in the concept of aesthetic experiences. Schusterman 1997. Aesthetic experiences are linked to evaluated processes, inherently valuable and in some ways pleasurable, to phenomenological occurrences, distinctively felt and identified amongst other sensations, and to instances of semantic qualities, meaningful. These dimensions as well as the concept of aesthetic experiences per se are not without criticism. With regards to evaluated processes, for example, the concept of beauty is central in most studies on aesthetic appreciation, e.g. Chaturji 2010. However, it is important to bear in mind that aesthetic responses to art and other classes of objects is much more varied. Although dance is predominantly received in the visual domain, it is important to acknowledge its other realms. Dance involves not just the eyes, but the entire body. Dance has thus been described as a multisensory, ephemeral, kinesthetic art, something 224 Julia F. Christensen and Corinne Jolie will discuss later in the chapter and is expressed in Table 12.1. Indeed, aesthetic experiences are not proposed to occur exclusively in response to the visual arts. Aesthetic experience is studied in response to sensory modalities other than vision are the tactile sense, Hinson and Nelson 1971, Silverthorne ETAL 1972, the auditory sense, Konechny ETAL 2007, Kornishiva ETAL 2009, and more recently through increased interest in dance, the kinesthetic sense, Calvo Marino ETAL 2008, Cross ETAL 2011, Jola ETAL 2012B, Neiman ETAL 2011. Clearly, we know through experience that a visual work of art can also provoke a kinesthetic experience, and a stage dance performance can also be visually pleasing. Reason and Reynolds 2010. Here we do not dissect different sensory modes of aesthetic responses. On the contrary, as it is particularly evident in the case of dance, we base our chapter on the assumption that aesthetic experiences are a combination of sensory responses, and that the potential of aesthetic experiences and therefore related aesthetic judgments are present across sensory modes at all times. Moreover, what is different between aesthetic experiences evoked through watching dance, or listening to music, and the sensations provoked by looking at an object of art is the continuation of sensory stimulation. The notion of time is a critical factor when attempting to capture aesthetic experiences in dance. In this chapter, we thus focus on the challenges that the predisposition to engage in aesthetic experiences in the form of a continuing multisensory, immediate, meaningful, and evaluative process poses on empirical research, as is the case when studying aesthetic processes in response to watching dance. We emphasize the relevance of employing dance stimuli in their original form, i.e. close to real-life experience, and back our argument up with recent evidence. We argue that every so often, and most likely due to attempts of experimental control and scientific reductionism and partly due to a lack of knowledge of the subject matter, art in general, Sylvia 2012, and dance in particular has been employed in such a manner that it was no longer recognizable as either art or dance. See Jola 2010, Jola ETAL 2011. In extreme cases, arguments made for using dance as a particular form of art can actually be lost by the way dance is employed. Enhanced ecological validity is a necessary step towards a better understanding of the psychological and neural processes involved in the aesthetic experience of dance. 1.2.1.2 Dissecting dance. Scientific reductionism. One common assumption grounding many scientific experiments is that complex systems can be reduced to their individual elements without changing the relevant conceptual properties of the elements as they were originally present in the complex system. Reductionism. The process of reducing and abstracting complexity to individual conceptual properties has been defended by the scientific community as a necessity in order to achieve reliable results in controlled environments. Consistent with more recent criticism of this approach in the study of visual perception, Felsen and Dan 2005, as well as in other fields that have an applied focus, e.g. Nern 2014, we question the extent to which reductionism is applicable to the observation of dance movements. See also Jola ETAL 2011, and encourage the use of genuine dance material. A reductionist approach can be considered a risk, given that it requires the scientist to know what the relevant conceptual dimensions are. Sometimes these are not necessarily known as in the case of aesthetic experiences. Sylvia 2012. Neuroaesthetics, as well as the study of spectators' responses to watching dance, is a novel field which has much work to do on understanding the relevant dimensional variables, but see Graham and Field 2007 or Chaturji ETAL 2010. Moreover, conceptual dimensions change over time, as has been apparent in general concepts such as the example given by Nairn, 2014, of the changing concept of gender, the changing interest and use of the concept of perspective in the history of art, e.g. Kukobi 1986, or the changing choreographic principles in dance, Butterworth and Wildschut 2009. In its extreme form, the manipulation of conceptual dimensions is itself the subject of a choreographer's artistic practice, Klein 2007. Not only does choreography define the work, it also demands cognitive engagement of the spectators in order to unfold such conceptual dimensions, as in conceptual dance, Jola 2010, see also section 1.2.2.1. Hence, complex systems in art and dance may be based on different relevant conceptual dimensions for each and every work. In addition, a reductionist approach focuses on explaining complex systems through the study of low-level causation. However, the relationship of the whole and its units is more complex and entails the possibility of top-down causation as has been shown even at the neuronal level, i.e. through adaptation. As outlined in more detail later in this chapter, there is significant evidence that aesthetic appreciation of an object relies on its context, its complexity, and spectators' expertise, all existing beyond the object's own features. Letter ETAL 2004, Locker ETAL 2005. Research thus far in empirical aesthetics of dance has provided a preliminary understanding of visual features that make an individual derive pleasure from watching dance. Nevertheless, we propose that it is possible to deepen our understanding through the use of more ecologically valid stimuli. Alongside the problem of identifying the conceptual dimensions relevant to this area, and the emphasis on low-level causation in reductionist approaches, there is a third concern which we must raise here, the frequently low aesthetic validity of dance stimuli in empirical aesthetics, which is based on the field's history. See also Cross ETAL 2011. The number of experimental studies that have employed dance stimuli to study the human brain and behavior has been increasing since Calvo Marino, Glazer, and colleagues, 2005A, seminal brain imaging work with dancers. Dance has since proved to be useful in studying how training in a particular domain of movement such as dance modifies the cognitive and neural structure of the brain. Blazing ETAL 2009, Hangi ETAL 2010, or how our brain tangos with or without music. Brown ETAL 2006. Predominantly, however, dance has been employed to study how movement expertise affects action observation processes in the passive spectator. Calvo Marino ETAL 2005A, Calvo Marino ETAL 2005B, Calvo Marino ETAL 2006, Cross ETAL 2006, Borks ETAL 2008. In general, these studies showed that neural processes of motor resonance in the so-called mirror neuron network are enhanced when the observed action is part of the passive observer's motor repertoire. For further information on mirror neuron theories in dance, see review Encephالus and Keller 2011. With the growth of empirical aesthetics and neuroaesthetics, Chaturji 2003-2011, dance has re-entered the realm of science as a genuine art form. Cross and Ticini 2011, 226 Julia F. Christensen and Corinne Jola ETAL 2011, Christensen and Calvo Marino 2013. Some of the earliest evidence on the neural underpinnings of the aesthetic experience derived from watching dance was published in Consciousness and Cognition in 2008, Calvo Marino ETAL 2008. The authors showed how enhanced processing in visual and sensory motor regions of the brain correlated positively with the subjective aesthetic judgment dance novices made about the movements watched outside a scanner when they were recalled for an additional study about a year later. A number of subsequent studies found further evidence for how specific aspects of a dance movement modulate the aesthetic experience. Cross and Ticini 2011. In this chapter we are specifically interested in how dance has been employed in these studies. Notably, the first experimental stimuli used in empirical aesthetics of dance were similar to the stimuli used in studies of cognitive neuroscience of action observation. Hence, because they were not informed by dance theory, they lack ecological validity. From a dancer's point of view, these stimuli have limited artistic quality and thus in their potential to trigger genuine aesthetic experiences in the observers. While one could argue that aesthetic aspects may have been less relevant in the exploration of brain processes involved in action observation, it is obvious that the aesthetic appearance of stimuli is crucial when investigating aesthetic appreciation. However, aesthetic processes are potentially automatic processes, and thus affect the manner in which stimuli are processed even when the experiment does not target aesthetic explorations. Although researchers are aware of the intricacy of dance and understand that dance is more than just a type of movement pattern, assumptions about dance are sometimes made that do not correspond to contemporary understanding within the domain. Hence, many researchers still use somewhat impoverished dance stimuli. We will be addressing what potential effects this can have. However, if one were to employ dance in its original form, many variables would remain uncontrolled. This chapter attempts to address in particular why a more ecological approach to studying the human brain and behavior is necessary, using the example of employing dance stimuli. 1.2.1.3 Is it still dance? As visible in Table 12.1, studies that refer to having employed dance in their research vary notably in their basic assumptions about what dance may reveal. Column 2, what dance is. Column 3, how it looks. Column 4, and which task is best employed to measure it. Column 5. For example, empirical psychological investigation usually starts with the rationale for the objectives of the study and the sensory stimulation leading to a clear description with the exact parameters of the experimental stimuli in order to allow reproducibility. This applies also for more complex, natural stimuli that need to be clearly documented. In our case, the style of dance that is used, for instance, should be linked to the objectives of the study and clearly defined. Notably, however, the stimuli are rarely available for full inspection. Further, several published papers that have used dance stimuli have defined dance in an unmethodical manner. We argue that the definition of dance provided by the authors is critical because it indicates the key features on which the selection and creation of the stimuli were based, and it further highlights which features of the stimuli were relevant for the research. Hence, it explains the purpose of using dance, rather than some other type of movement, and also offers insight into what level of understanding of dance was the basis for the study. This, in turn, can reveal the artistic quality of the stimulus material, which again is particularly important for empirical aesthetics. Finally, it is worth noting that the subject's task, last column, has a large impact in neuroaesthetics on how stimuli should be contextualized. Letter ETAL 2005. For example, asking how tiring a movement appears may relate more to a different subjective and neural signature than when asked how much a person likes what he or she sees. We will describe this in more detail at a later point in the chapter. In Figure 12.1, we also provide a visual representation of the evolution from simple to more complex dance stimuli as notable in Table 12.1 over the last 10 years. Reviewing the definitions of dance in Table 12.1, there appears to be a tendency in many instances to oversimplify dance and define it merely as a type of movement pattern. In addition, when considering some of the stimulus materials used to date, one may come to the conclusion that scientists often wrongly assume that everybody knows when a movement is a dance. While this is probably true for informal social dances, it is certainly not the case for certain types of classic, formal, and postmodern dance movements, particularly when taken out of their normal contexts. In addition, a significant portion of the studies provides no definition of dance, and only a few studies describe the specifics of the particular dance style employed. In fact, the dance styles used in cognitive neuroscience and empirical aesthetics research to date are not only very different from each other in the types of movements or their repertoires, but also different in their function, social meaning, and origin. Hence, dance's meaning for participants in a study is not necessarily shared by a different study participant. In order to design a study employing dance as a means to study the human brain and behavior, it is important to understand what exactly makes a movement a dance, and to acknowledge that dance is something unique and thus very different from other kinds of movement patterns. It is therefore going to be very helpful for us to start with a thorough definition of dance. 12.2 Defining dance. 1.2.1 Dance is a social phenomenon according to the online Oxford English Dictionary's definition of dance. A dance is composed of a series of steps and movements that match the speed and rhythm of a piece of music. That dance steps and movements can be considered either as an activity, which can be a social gathering, or as an art form is also noted. The clarification of the role of the movement is important because, although the movement is arguably the most prominent characteristic of dance, definitions such as a person moving rhythmically to music, or a moving body in time and space, are not sufficient to describe dance. Moreover, movement-focused definitions are not applicable to many contemporary dance forms. For instance, conceptual dance works may not contain much movement at all. In Ivana Muller's While We Are Holding It Together, the dancers stay still for almost the entire performance of dance should thus include the functions of the specific type of dance used, e.g. emotional expression, creative engagement, rituals. Furthermore, it should take into account how these are achieved. This includes the complex interplay of the movement, the dance, with other parameters, the so-called strands of dance, e.g. performer, sound, space, costumes, lights, as well as the context, e.g. location or historical, social, and political position, the socio-cultural background and experience of the spectator, through which spectators and participants experience the meaning of the dance. Even when dance movements are abstract and form with no obvious everyday propositional or referential meaning, such as fist shaking, movements of longing, gestures like putting a hand on the heart, etc., they still convey messages and emotions to the spectators, whether intended or not by the dancer. In other words, when compared to other skillful movements such as those prevalent in sport, dance is unique because of these three key elements that unfold together: purpose, compositional strands, of which movement is one, and context. As with other art forms, the main purpose of the choreographer is not necessarily to produce a beautiful dance piece consisting of aesthetically pleasing movements. Clearly, the mastery of movements is the main goal in the early years of dance training. Over the last century, one could indeed observe a general tendency towards increased physical virtuosity, from new dance styles performed mostly by young people, e.g. hip-hop, breakdance, to established dance forms, e.g. classical ballet, which are supposedly perceived as more beautiful. Ducati ETAL 2009. For contemporary dancers, risk-taking is an important aspect of their practice as well as the drive to acquire skillful athletic movements. Dumont 2009. Dance is, however, more than a technical exercise in mastering particularly difficult movements unlike rhythmic and artistic gymnastics, for example, where the skillful execution of a range of increasingly difficult types of movements is the ultimate goal. In early neuroscientific studies using dance movements, dance was simply used to study, for instance, mirror neuron mechanisms for intransitive movements, movements that are not directed towards an object, compared to transitive movements, towards an object, goal-oriented actions. It is worth noting that dance movements can be intransitive but still meaningful. In fact, from a dance expert's point of view, it is clear that the conditions under which a movement is without meaning are rare. Furthermore, intransitive movements can be propositional or non-propositional. In speech production, for example, non-propositional speech refers to utterances of overused expressions/phrases. In movement terms, however, propositional movements are those that have culturally recognizable communicative intention, such as waving, nodding, or shaking the head, stretching out the arms in an expression of longing, etc., while non-propositional movements are abstract. The latter may be meaningful as well, but they achieve this without having a clear cultural meaning in the form of a gesture. In dance, we can find both propositional as well as non-propositional movements. While some dance forms do include the use of propositional movements, such as certain classical ballets, e.g. Les Sylphides, other dances predominantly consist of non-propositional movements, such as numerous contemporary dance performances, e.g. creations by random dance of moving towards ecological validity and empirical aesthetics of dance 239 Wayne McGregor, see May ETAL 2011. Hence, dance employs different forms of actions, transitive, intransitive, propositional, non-propositional, gestural, physical. Finally, movement types are closely linked with the music and the other strands of the dance. The music, scenery, costumes, lighting, and other special effects are as previously indicated strands of the dance, which add to the experience of the spectator. Preston Dunlop and Sanchez Colbert 2010. As early research was very much dealing with movement, it is only recently that the strands that crucially influence the form of dance have been brought into focus. It is likely that spectators' aesthetic experience, including their affective, aesthetic, and kinesthetic responses, are specific to different types of dance forms, and therefore careful choices need to be made when using such stimuli, whether in the study of action observation processes or in neuroaesthetics. In addition, it is important to consider that dance happens in a specific context. Elements of the context may be, but are not limited to, its location and its historical, cultural, and socio-political position. The context may be the key to truly understanding dance, especially as far as contemporary dances are concerned, unlike acrobatics, which is astonishing to watch, no matter where, when, and in what context. In acrobatics and some 21st century forms of dance, context is employed to increase physical challenges. However, it does not add any other meaning to the movement beyond demonstrating the capability of the performer. Thus, dance differs from other movement because I. It has a communicative intention. 2. This intention is brought to the observer by different constructs of motion accompanied with other strands. 3. It happens in a specific context whose elements may be the key for the understanding and cognitive, and emotional, mastering of the dance. This combination makes dance unique. How dance and its meaning is received and processed in the mind of a spectator under these premises is the objective of the next section. 1.2.2.2 Modeling the aesthetic experience of dance in dance. Aesthetic attributes are generally assigned to the dancer's movements. Nevertheless, as indicated above, many other elements contribute to the aesthetics of dance. These include, but are not limited to, part of the stage setting, lighting, clothing, objects on stage, and their arrangement, and so on, and the synchronicity between dancers or parts of the dancer's body. Even when movement is the most relevant feature of dance, aesthetic decisions about all strands are necessarily to be made when staging dance performance. To a dance expert's eye, it is evident when beautifully crafted movements are situated in a performance context that lacks coherent artistic choices. In other words, a spectator's aesthetic experience is the outcome of a holistic impression of all elements of a given performance. Importantly, the aesthetics of the dance itself, the choreography, i.e. the movements and their composition, the staging of the performer, i.e. the performer's presence, as well as the combination of movement and music, are dynamic elements. Thus, dance's aesthetic appearance unfolds and decays with time. Despite its fleeting character, dance can evoke resonating aesthetic experiences of emotional, affective, kinesthetic, and visual aesthetic. 240 Julia F. Christensen and Corinne Gilla forms in Spectators, Reason and Reynolds 2010. But how to begin to account for the aesthetic contributions of so many elements at these different levels? A good starting point might be the psychological model of aesthetic appreciation proposed by Letter and his team, 2004. They, Letter ETAL 2004, sought to understand the processes involved in an aesthetic experience in response to exposure to an artwork and how they trigger aesthetic pleasure as well as the formation of aesthetic judgments. Since the model was specifically designed to explain the aesthetic experience derived from modern visual art, it adopts a very broad view when taking into account aspects of the context, the perceiver, and the overall situation in which an artwork is encountered. By describing the interrelated levels of visual and cognitive processes of looking at art, it indirectly illustrates the appreciation of the multilayered nature of an artwork. Applied to dance, Letter and colleagues, 2004, model requires further development. As already indicated, one very distinctive feature of dance, as compared to the visual arts, is its temporality. Dance unfolds over time and so does the spectator's aesthetic experience with it. While the processing stages of the original model, perceptual analysis, implicit memory integration, explicit classification, cognitive mastering, evaluation, affective processing, and aesthetic judgment/emotions, are adept in the reception of dance works, the temporal dimension needs to be included. The interrelated processing stages are thus not only influenced by variables such as the previous experience of the individual, including specific knowledge about the particular artwork, general declarative knowledge about style and content, personal interest and taste, the social discourse and context in which the aesthetic experience takes place, museum, gallery, experiment, etc., but also intertwined by the continuing flow of motion. At a given moment in time, viewers may be in the process of classifying a particular movement they see according to previous knowledge, explicit classification, while they could also be at the stage of cognitive mastering regarding previous dance movement sequences whose deeper meaning they are in the process of grasping, and they may also be undergoing a comparative process of the predicted movement with the movement seen. All these processes are constantly updated, receiving new inputs as a dance unfolds. Judgments and emotions are thus modulated by the continuous updating by experience. Below we outline the specific findings of the continuous influence of context, movement, and experience undergone when watching dance, according to the 6 processing steps of Letter and colleagues, 2004, model. 1.2.2.1 Input. Pre-classification and context. The historical and social context of a dance work is highly relevant to its appreciation and understanding. For example, when focusing on theater dance, as its name suggests, the theater setting is of relevance. Furthermore, while the particular movements of a dance recording may match those of the live dance as it has taken place in the theater, spectators' experiences for these two viewing formats are not the same. This has been supported by recent empirical research by Gilla and colleagues, 2012a, 2013a, who measured spectators' internal motor resonance when watching dance live and on video. The authors assessed spectators' motor resonance through the indirect measure moving towards ecological validity and empirical aesthetics of dance. 241 of motor corticospinal excitability, whereby the amplitude of motor hook potentials in the finger and the arm muscle groups induced by transcranial magnetic stimulation, DMS, indicate the level of corticospinal excitability. In the first study, Gilla ETAL 2012a, visual expertise in ballet was found to enhance muscle-specific motor resonance when watching a classical ballet solo live. This finding expands previous research on dancers' physical expertise. Furthermore, it partly contradicts previous findings from other fields than dance, i.e. basketball, where visual expertise was reported to be insufficient for muscle-specific motor resonance, Alai ETAL 2008. In a second study, Gilla and Grobraz, 2013, compared two groups of novices watching ballet solo, a classical Indian dance solo, Bharatanatyam, and an acting control condition either live in a rehearsal studio or on video in the laboratory. Not only did the novice live spectator group show enhanced motor corticospinal excitability for the gestural prone Indian dance, they also reported to have liked watching all performances more than the video group. In addition, the liking ratings differed significantly between the individual performance types when watched on video. This is of huge relevance, as it indicates that in a video setting, affective components such as enjoyment could modify the general affective state and potentially act as a confounding variable, leading to different aesthetic experiences as well as impacting upon neuronal processes. Indeed, a number of recent studies support a general effect of liveness on spectators' responses to the observation of everyday actions, Jardelin and ETAL 2001, Shimada and Hiraki 2006. Overall, it seems that at least for novice spectators, the context of a live performance changes their responses to watching dance. It is thus important to look further at how effects of expertise as have been reported in earlier studies may have been affected by the artificial setting of dance when taken out of its theater context. It is worth noting that most studies recorded dance movements in a rehearsal space, where the gap of familiarity between spectators with physical expertise, who were very likely to have danced in similar spaces, and novices, who may have never been in such spaces, can be expected to be large. Hence, studying live face-to-face interaction may be the big challenge of future research in cognitive neuroscience, as it may require further consolidation as a necessary condition for producing empirically valid and reliable results. Repay ETAL 2010. Additional aspects of spectators' experiences could also include the specificity of an event, the sharing of the experience with other spectators, related expenditures, e.g. ticket costs, traveling expenses, and so forth. Hence, the social context stands out as particularly relevant in the case of dance. The theater setting in which dance is commonly consumed provides a context of vivid social interaction and discourse, in the intervals or during the performance where the spectator perceives other spectators' reactions around him/her. Besides, the presence of both the performer and the spectator is specific in a live setting. A good performer uses the feedback from spectators, he plays with the interaction. Thus, he will adjust the performance to the spectator's needs. Optimally, this means that each spectator will be presented with the performance expression that at his or her own level of intensity. This possibility has, however, not yet been empirically verified. 1.2.2.2.2 Evaluation processes. By perceptual analyses, perceptual variables that have been found to affect aesthetic responses include contrast, visual complexity, intensity, brightness, saturation, size, color, symmetry, and grouping. According to Letter and colleagues, 2004, model, preferences will vary according to changes in these perceptual dimensions. For instance, curves and symmetric shapes have been found to be preferred over lines and edgy shapes in visual art. Tinyo and Letter 2009, Letter ETAL 2011. Clearly, some of these dimensions are also prevalent in the context of dance and their relevance has been discussed. For example, symmetry, Hagendorn 2005, Aronoff 2006, or the edginess of shapes, Deprati ETAL 2009. Using dance photographs, Deprati and colleagues, 2009, found evidence that more vertical dance positions, i.e. positions that involved a higher extension of the legs, were liked more than less vertical ones. The authors related their finding to a general preference of certain shapes over others, independent of the particular dance position. Dance further makes use of the lighting as a stylistic element, colors, costume, textures, and the like to highlight specific visual aspects of the movements and to capture spectators' attention. Undoubtedly, different levels of luminance influence subsequent cognitive processes. Sometimes, different light settings are so extreme that video recordings from an original stimulus, i.e. a live performance, cannot be used without modification for empirical research, e.g. too dark for visibility. Thus, for a truly ecological approach to dance, further studies are needed in order to determine how different perceptual stimuli properties can influence the appreciative process of the individual when contemplating dance. A better understanding of perceptual parameters will enhance targeted control in the service of experimental rigor, while still allowing a genuine aesthetic experience of dance to unfold. 1.2.2.2.3 Evaluation processes. 2 Implicit memory integration in the aesthetic appreciation of visual artworks. Tinyo and Letter 2009, as well as that experience when watching dance. Calvo Marino ETAL 2008, Zhang and Pollock 2011. Novelty and familiarity with the stimuli were found to influence motor resonance significantly as well as influencing aesthetic appreciation. Cross and Ticino 2011. Hence, a careful control of participants' previous dance experience is important. Notably, a large number of potential experimental participants have had formal dance training in their youth. While they may not be presently practicing any dance, their prior exposure to normally a particular kind of systematized dance training constitutes at least implicit and/or embodied knowledge of a given dance style, if not also extensive explicit knowledge. An example of how implicit knowledge influences low-level perception of a dance piece was offered by Stevens and colleagues, 2010. The authors demonstrated that expertise with a dance piece led to anticipatory eye movements when watching a section of a dancing duo on video. Another important consideration is the spectator's cultural knowledge and the environment in which the study is carried out. For example, traditional Indian dances are displays of popular fairy tales and movements from them are bound to elicit related memories in an individual with an Indian cultural background. Therefore, an experimental participant from an Indian cultural background will perceive more or more refined associations in an Indian dance movement or position than a Scandinavian participant with no experience and or knowledge of Indian culture. Thus, even if the research question is not primarily about the content of a dance, specific dance stimuli will elicit specific cognitive and affective processes in some individuals but not in others. Some studies have investigated the effects of culture on action observation processes, DC and Theory 2007, Molnarchikov ETAL 2007, with, however, contradicting results. Further studies are needed to improve our understanding of when and how top-down processes are shadowing the aesthetic experience. Explicit knowledge of paintings was found to affect naive spectators' subjective preferences. Specifically, participants' aesthetic judgments have been found to vary according to whether the painting's titles were presented or not. Letter ETAL 2006, Kirk ETAL 2009, 2. Whether information was given about the painting style. Letter ETAL 2007, Augustin ETAL 2008, and 3. Whether participants were made aware of the artist. Letter 2001. Hence, explicit knowledge influences the evaluation of an artwork. Letter and colleagues, 2004, proposed that experts classify an artwork based on prototypes. No research has yet investigated prototypical classification in dance. It is worth noting that the early study of motor expertise in certain dance styles, e.g. Calvo Marino ETAL 2005A, 2005B, has compared two dominant styles, ballet and capoeira, but has not investigated prototype perception. However, we suggest that dance professionals might perceive dance according to their individually formed prototypes, subject to training and personal taste. Hence, a movement may represent a perfect prototype, and experts may evaluate variations of that movement on the basis of their prototype representation. According to Letter and colleagues, 2004, non-experts' aesthetic experience is more heavily based on stereotypes than experts' aesthetic experience. Research into the aesthetic appreciation of dance would thus benefit greatly from knowing about people's stereotypes about dance in different dance forms. We argue that the dance stimuli used in experiments should be regarded by experts as of high artistic quality, adhering to style and content conventions, independently of the research question. Only when a movement or dance posture is correct, i.e. of high quality according to the style used, will expert spectators be able to engage fully in aesthetic contemplation. Observation of poor quality movements or postures may lead to a fast and frugal aesthetic evaluation or a response of disgust/disagreement. 1.2.2.2.5 Evaluation processes. For cognitive mastering and evaluation according to Letter and colleagues, 2004, the successful perception and processing of an artwork will ultimately lead to a cognitive mastering, which is the level at which an individual understands the artwork. Understanding is supposedly based on art-specific and/or self-related interpretation and can lead to either a positive experience of liking or a negative one. The individual can come to the conclusion that she doesn't like what she sees. 244 Julia F. Christensen and Corinne Jola in Dance. The cognitive mastering based on art-specific interpretation is likely to be influenced by elements of the context that help relate the dance to its historical and socio-political framework. Goulart and River 2013. The temporal evolution during dance performance is also particularly relevant here as different processing stages are constantly influencing each other, bottom-up as well as top-down. Furthermore, dance often has a clear narrative, i.e. the storyline, and discourse, the conceptual metaphoric, expressive intention of the artist. A spectator can only comprehend those aspects as the dance unfolds over time. Thus, accessing the discourse of a dance is likely to be possible only if a full performance is watched. In previous research that used short dance stimuli, approximately 3 seconds, this level of cognitive mastering may not have been reached. We thus suggest adding to the art-related and self-related interpretation within work-related interpretation. 1.2.2.2.6 Effective and emotional processing. Many studies in the field of empirical aesthetics of paintings focus on the effective responses participants derive from looking at them. Vartanian and Goel 2004, Cooking DETAL 2009, Vartanian 2009. For dance, such empirical findings are still elusive despite the fact that choreographers frequently seek to craft works that convey emotional valence to the observer. Some suggestions have been made that both novelty and, contrarily, familiarity of actions lead to emotional positive effective responses in the observers, e.g. Hagendorn 2010. Further, watching different types of non-dance everyday movements has been found reliably to modify physiological as well as subjective emotional experiences. DeMeyer 1989, Atkinson ETAL 2004, DeGelder 2006, Phelan ETAL 2007, Atkinson ETAL 2012. Some of this research has also harnessed dance movements. Dittrich ETAL 1996, Hedgemada ETAL 2000, Pollock ETAL 2002, Kammer ETAL 2003. This indicates that emotion is indeed reliably induced when watching dance. However, so far no emotion-related brain activity has been found in neuroaesthetics experiments with dance movements, with the exception of Grobrock et al. 2012. It is possible that the reason for the lack of evidence for changes in the affective, i.e. subjective, physiological, and neural responses resides in the stimulus material used in research thus far. 1.2.2.7 Recapitulation of the model. The evaluative stage is obviously not only attained at the very end of a performance but forms part of the processing stage as the spectator is constantly going through and updating in response to the unfolding dance on stage. The cognitive mastering of one sequence of movement may be successful at one point of time while another one is not, except if the whole piece is watched. Insight about the meaning of a particular sequence of movements may reveal itself at a much later point in time of the performance than in the very moment of display. The interacting and constantly updating nature of the whole aesthetic intercourse between the spectator, the dance, its different strands, and the other elements of the context is represented in the figure with the often bidirectional arrows. Full-length and complete ecological stimulus material certainly provide the best grounds for such a genuine aesthetic experience to unfold. Moving towards ecological validity and empirical aesthetics of dance 245 12.3 dance employed as ecologically valid stimuli aesthetic episodes, whether in a museum or laboratory, have basic features in common. They formally begin when a viewer comes into contact with a particular artwork and end when the viewer ceases to explore it. Viewers in both settings usually encounter a series of artworks. The experimenter, like a museum curator, selects the set of stimuli in accordance with a particular theme or goal. Indeed, the boundary between laboratory and museum is blurred when visitors are formally asked to rate paintings at an exhibition. Tem 1983. The structure of an aesthetic episode as an encounter between a viewer and a stimulating object makes it amenable to empirical study. Kupchak and Gabadis 1988, pages 1-2. Kupchak and Gabadis, 1988, provide an interesting analogy between aesthetic episodes evoked in art institutions and those experienced in laboratory settings. As the authors state, the scientist would be considered a kind of curator, selecting the theme displayed as well as the individual artworks. However, in many instances the scientist does not display the original material. Moreover, the works are often modified in order to test particular hypotheses. The interference of the scientist with the artwork itself could cause considerable alteration of the original, and sometimes its destruction. In the case of empirical aesthetics of dance, the stimuli used in research have rarely been related to original choreographed works. One could thus argue that there is no ecological validity of such stimuli as they are not only out of context but they have no context at all. There are three aspects to the validity of a measurement. Internal validity designates the degree to which causal relationships between independent variables exist. For high internal validity, research conditions such as stimuli or the context must be controlled, and any potentially confounding variables accounted for completely. External validity is confined to the generalizability of the results, i.e. whether or not the same results would be obtained in a different context, time, and with other participants than those included in the study. Ecological validity refers to whether or not the results obtained under laboratory conditions are applicable also to the natural context where the objective phenomenon of the study usually unfolds. Overall, when we request more ecological stimuli for empirical aesthetics of dance, we refer to stimuli that more reliably capture dance as a social artistic phenomenon and that are capable of eliciting a genuine aesthetic experience in the observer. Undoubtedly, studying the neural processes of observation or appreciation of original dance is more challenging than studying the same processes when looking at a painting or listening to music. Paintings have the benefit of being static over time, while looking at a particular painting, and music has infinite degrees of freedom, in the sense that any note can follow another. Dance works, however, change over time, while watching, and have numerous but biologically limited degrees of freedom. Not every posture can follow another without physiological transition. The scientist faces these challenges when attempting to use ecological valid stimuli in dance. Other associated issues are organizational, i.e. accessing theaters and coinciding with their schedules, financial, filming, lighting, and 246 Julia F. Christensen and Corinne Jola space is expensive, interference, of non-controlled environments, unpredictability, at any one performance, unforeseen things can happen and they may not be repeated, and analysis issues. The analysis of complex data of long duration is not possible using conventional approaches. Nevertheless, some pioneering studies showed that it is possible to use ecological valid dance stimuli when studying spectators' motor resonance or aesthetic appreciation, with varying degrees of success, e.g. Jola et al. 2011, Grobrock et al. 2012, Noble et al. 2014, Jola et al. 2013a, 2013b. While some of these studies showed less clear and potentially unreliable results, they provided a valuable testing ground for our understanding of dealing with complex natural stimuli. We hope that researchers are encouraged to explore such approaches further. For example, Jola and colleagues, 2009, measured motor corticospinal excitability in dance spectators when watching a live technical rehearsal, including light, costumes, orchestra, of The Sleeping Beauty in the Theatre Royal in Glasgow. This study did not show the expected results, i.e. enhanced motor simulation for physically challenging movement phrases compared to theatrical moments without dance, but instead showed a tendency for a decrease in motor simulation over time. The data had, however, several outliers and a more controlled study would be required to test the possibility of reduced motor simulation over time. We thus support the use of video recordings of genuine dance performances as a valuable alternative to live performances. This allows improving the quality of the data through a better control of the complex environment while employing stimuli of long duration. Short video clips have been employed most frequently to study action observation of dance movements, e.g. 2 seconds, cf. Zhang and Pollock 2011, 3 seconds, cf. Talvamarino et al. 2005a, and 5 seconds, cf. Cross et al. 2006. Stimulus materials in such studies are commonly very thoroughly controlled regarding all information which could represent a distraction from the movement, such as color, music, stage props, and the face of the dancer. All of these are commonly removed. This enhances internal validity as potential responses to the dance that could otherwise be modulated by the addition of these strands of expressive information. At the neural level, a face consistently triggers the activation of the fusiform gyrus, i.e. the fusiform face area. Ken Wisher et al. 1997. Color helps object recognition and its processing requires distinctive and additional neural pathways when compared to black and white processing. Superior parietal lobule and precuneus bilaterally, the right hippocampus, and the right fusiform gyrus, V4, Bremau et al. 2010. Finally, research on music has shown that it clearly has its own potential to induce emotion. Blood and Zader 2001, Salimpo et al. 2009. The use of such short stimulus durations is not exclusive to the field of action observation. In neuroaesthetics, dance stimuli of short durations have also predominantly been used. As the characteristics of dance movements can change considerably over time, short sequences do indeed allow for a more uniform selection of movements, and participants' reactions can be measured in response to specific movements. Talvamarino et al. 2008, Talvamarino et al. 2010, Cross et al. 2011. A conceptual concern about short stimuli is that the artistic quality is constrained. We argue that for a genuine aesthetic experience to unfold, more than 3 seconds, of moving towards ecological validity and empirical aesthetics of dance 247 continuous dance movements are necessary. This allows the spectator to follow a narrative as well as the discourse level of the choreography. However, short stimulus durations are methodologically better suited to neuroimaging as well as behavioral studies. Nevertheless, with novel analyses methods that focus on the time components, longer stimuli become feasible, e.g. Orts et al. 2008. Therefore, if the methodology of a chosen study requires short stimulus durations, then a careful selection of the stimuli should include a dance professional in order to select stimuli that are artistically as expressive as possible, in spite of being only a couple of seconds long. For this, it is especially important to respect the sequencing of the dance movements. Non-dancers are likely to be less accurate than dancers in sequencing dance movements correctly. The elicitation of an aesthetic experience from dance movements depends crucially on the choice of particular movements and their being started and completed adequately as specified by the audience's perception. Noble et al. 2014. Within the field of neuroaesthetics, long dance video clips have been chosen more frequently than short dance clips as stimuli, e.g. 3 minutes, cf. Grobrock et al. 2012, 5 minutes, cf. Jola ETAL 2012A, 6 minutes, cf. Jola ETAL 2013A, 2013B, and even 2.5 hours, cf. Jola ETAL 2011B. Clearly, longer stimuli allow a more holistic approach to the actual unfolding aesthetic experience of dance as described earlier, i.e. narrative and discourse. Pitfalls of such an approach using long complex stimuli presentation are that they do not allow high levels of control and they require novel types of analyses. Nevertheless, what is an adequate level of experimental control in the stimulus material for neuroaesthetic studies is critically dependent on the objectives of a study. If the research question is about the genuine aesthetic experience of dance, then longer, more ecologically valid stimuli should be presented and later combined with psychophysiological, e.g. respiration, skin conductance, galvanic skin response, GSR, heart rate, electrocardiogram, ECG, and subjective measures, e.g. visual analogical scales with an online slider option, or verbal reports, that accompany the experiences. Similar qualms as those raised with regard to the long video clips have been voiced about the use of live dance performances as a suitable location for neuroaesthetics of dance research. The clear advantage of this approach is that the performance is fully ecological and also includes the very relevant social and communicative aspect of an evening at the ballet, in addition to measures related to the CO presence of the performer and the spectator. In other words, the experience is genuine and only subtly altered due to the apparatus of the experiment. Stevens ETAL 2009, Jola ETAL 2011A, Jola and Grobross 2013. Live performances will be experienced differently by each participant. While this may at first sight represent an issue, there is an important aspect that deserves a second look. Dancers in live performances adapt their dance to the time of the performance, time of the day, historical point, light, etc., and critically in response to the atmosphere created by a particular audience. It may be a very daring suggestion, but consider the following as a tentative working hypothesis. When dancers actually tailor their performance to the particular audience they have at a given time, they will automatically modulate different aspects of 248 Julia F. Christensen and Corinne Jola their dance according to the needs of that particular audience. This means that in the end, a number of performances of the same piece of dance will have been performed with different expressive and artistic qualities depending on the feedback the dancers received during the performance. Some performances will have been stronger because the audience needed more stimulation, while other performances may have felt more suppressed. Thus, in the end, the same piece performed at different times and in front of different audiences will have elicited a similar level of aesthetic experience in the observers because these observers were receiving the performance tailored to their individual stimulation requirements. Hence, tentatively, we could say that responses obtained by means of such a setup are actually more internally valid than those elicited by watching a video, because this setup ensures that each audience member is being moved according to his or her own needs. Jola and Grobross 2013, Jola ETAL 2011A. Such an experimental should be approached with caution though, and only under the supervision of dance professionals who can ensure that the experience is genuine. Besides, adjustments are likely to depend on the number of people in the audience, on the importance of an audience-dancer interaction of the particular dance style, and on whether the dancer is sensitive and skilled enough to actually tailor the performance to the particular needs of an audience. Finally, dance photographs have been used as stimuli. These have varied from very controlled static academic dance positions in front of a neutral background, with neutral clothes and the dancer's face blurred out, Calvo Marino ETAL 2010, to photographs from genuine performance settings, reproduced in color, including the dancers' faces in costumes, to Prati ETAL 2009, Jola ETAL 2012B. Concerns about this kind of stimuli are mainly conceptual. First, photographs are not strictly speaking dance, they are a type of visual art. Second, especially if static academic positions are used, i.e. positions that are from the basic syllabus of movements and positions of a dance style, this is not technically speaking dance. Dance positions are merely the tools of the trade. Accordingly, they are of questionable artistic quality when presented in isolation. However, photographs can be valuable experimental materials. By controlling the temporal dimension of the dance to a minimum, a dance photograph is only a snapshot of a distinctive moment in time of an unfolding dance. It allows studying spectators' reactions to particular, well-isolated features of a dance movement. Thus, in a recent kinesthetic empathy study it was shown how an embodied response of movement could be elicited through ecological dance photographs when particular parameters such as movement direction, horizontal versus vertical, were carefully controlled in the stimulus materials. 12.4 Challenges past and present. We have shown that dance stimuli can and have been employed in experimental research in and beyond neuroaesthetics. Other scientific investigations that have already benefited greatly from using dance as a movement stimulus did not aim at making assumptions about dance itself or the specific dance styles used. Dance in these cases is just a tool to study the human brain and human behavior. We argue, however, that since aesthetic appreciation moving towards ecological validity and empirical aesthetics of dance 249 processes are inherent, aesthetic experiences are always attendant when exposed to watching dance. Hence, careful creation and selection of stimuli creation is crucially independent of whether dance is the main subject of the study or not. In order to meet inherent aesthetic expectations, we argue that high ecological validity is needed when dance is employed in empirical research. As outlined, this naturally poses several challenges. In this final part, we suggest how to overcome these challenges when choosing an ecological approach to dance as an experimental stimulus. In many cases, scientists have been very scrupulous and have carefully controlled for interfering variables by employing a reductionist experimental approach. For dance stimuli, however, our arguments go in two seemingly opposing directions. On the one hand, dance stimuli need to be better controlled, for example, for motion parameters. On the other hand, dance stimuli need to be presented closer to how they are in real life, something which inherently introduces an increase in potentially confounding factors. Clearly, the two arguments are related, i.e. the higher the ecologically validity, the more uncontrolled variables are included, versus the higher the control over confounding variables, the less likely the stimuli resemble what we perceive as dance. Furthermore, we have not yet discussed that beyond the choice of the stimulus content and presentation, aspects of the experimental conduction are crucial. In other words, the instruction given to participants as well as the participants' tasks can modify aesthetic appreciation. Finally, as most studies showed differences between experts and novices, it is hard to dispute the fact that the participants' deemed graphics, e.g. experience, requires attention. For example, the aesthetic appearance is especially relevant for experts. Also, as dance is not acknowledged to be on the same artistic level as visual art or music, it is relevant to consider possible prejudices when testing novices. The particular parameters that need to be better controlled relate to the multiple interrelated strands of dance, i.e. movements, music, costume, presence, lighting, narrative as introduced in section 12.2. The combination of strands is particularly relevant for ecologically valid stimuli as dance is often performed with music, costumes, etc. The control for all of these parameters, however, is challenging and as yet we know little about how the individual strands in combination with movement affect neuronal processes when watching dance. Scientific focus on this art form only began about 10 years ago, e.g. Calvo Marino ETAL 2005, Jola and Mass 2005. Hence, we have only recently begun to disentangle how relevant parameters such as features related to movement, music, and slash or sound, level of performance, cultural background of performer and spectator, determine neuronal processes when watching dance. If scientists were to create dance stimuli based on knowledge about perception and cognition from basic science, for analogy see Hagendorn 2005, 2010, Jola 2010, we would end up with stimuli that are not recognizable as dance. It is not only the movement dynamics that have affected motion perception, Pollock ETAL 2001, Lagerlof and DKRF 2002, but also the pure quantity of motion, Noble ETAL 2014, the predictability of motion, Cross ETAL 2011, the duration of motion, Jola ETAL 2011B, and whether the dance contains gestures or abstract actions, Jola ETAL 2012A, Jola and Grobross 250, Julia F. Christensen and Corinne Jola 2013. All have an influence on action observation processes. However, further studies are needed to understand their role in aesthetic appreciation. For instance, the movement direction seems to have a great impact on the aesthetic appreciation of dance, Calvo Marino ETAL 2008. A recent study by Jola ETAL 2012B further supported this finding. Participants responded to experience a stronger kinesthetic sensation in vertical compared to horizontal implied dance moves. Hence, not only does one have to consider that processes related to movement perception may be influenced by the quantity of motion, but also may be influenced by the direction of movements. Hence, one should control for such potential confounding factors if they are not already implemented as experimental factors. We have also shown that the background of the dance stimuli has varied extensively across existing studies. A dance recording taken in a ballet studio often shows bars and mirrors. The bar is a tool used during classical warm-up exercises in ballet. The dancers hold onto the bar with one hand to support their balance, integrate it as a reference point for postural alignment, and use it as a tool for stretching exercises. The bar is thus a very familiar element of training in particular for ballet dancers. Hence, a bar in the background may be pleasurably nostalgic to some people, with memories of idling or stretching, eliciting unintended representations in a mindset of rehearsal and daily training, but may be entirely meaningless to others. One could argue that it has the potential to enhance motor simulation processes due to its association with a training context. Therefore, the visibility of bar or mirror acts as a reference to a training context and does not qualify as a natural setting for watching a professional dance performance. We hope that we have illustrated with this example that the context in which an aesthetic experience usually unfolds needs careful consideration and preparation. A number of very recent studies investigating spectators' responses to watching dance performances have indeed used recordings from the stage. Grove et al. 2012, Reason et al. In review. Regarding participants' instructions, it is important how the dance movements are brought to the participant as well as how the participant is brought to the dance. Instructions that emphasize the artistic nature of the experiment are one way to ensure that the participant understands that aesthetic expectations are welcome, especially if the experiment takes place in a laboratory and is artificially controlled with the risk of deprivation of artistic features. As shown in a neuroimaging study using paintings, Kupchak et al. 2009, neural activity in response to visual artworks depends on the participant's task. When participants were asked to engage in an irrelevant object identification task, activity in the fusiform gyrus, right, was found, in accordance with the object identification task. However, if participants were in the mindset of aesthetic appreciation, enhanced bilateral activity in the insula was found, a region crucially involved in effective processing. Interestingly, brain imaging studies of action observation and dance appreciation show similar cortical activity in visual, parietal, temporal, and frontal areas. For review see Christensen and Talbot Marino 2013, whereas evidence for limbic structures involvement, i.e. structures important for effective processing, in aesthetic experience has been shown frequently. Brown and colleagues, 2011, for example, showed in their meta-moving towards ecological validity and empirical aesthetics of dance 251 analysis that the insula appears to be key as it was found to show increased activation in so many studies on aesthetic appreciation. Forgas, 1995, proposed the affect infusion model, AIM, which suggests that current mood and affective priming has an effect on judgments. According to this view, judgments to non-familiar stimuli are particularly likely to be influenced by affect infusion. For empirical aesthetics, this means that for artworks one has little knowledge or no knowledge about, the current affective state will influence one's judgment more than for artworks with which one is familiar. This was recently experimentally assessed by means of a priming paradigm where happy and disgusted facial emotional expressions were presented with very brief stimuli onset asynchronies, SOA, just before instances of unknown paintings by Pollock. The happy primes increased the aesthetic experience, while disgust primes reduced it, assessed by means of subjective ratings of liking on a Likert scale, Fluxus et al. 2014. This shows that aesthetic judgment crucially depends on the spectator's affective state, be it triggered by the artwork itself or by some stimulus which is independent and may even be relevant to the artwork itself, as were the faces in the case of the mentioned study. Thus, the affective state prior to the exposure to an artwork potentially forms part of the whole mindset an individual is in when he looks at an artwork. Moreover, regardless of whether the mood or affective state prior to the exposure to an artwork is positive or negative, it is crucial that there is effective engagement with the artful object. Higgins, 2006, argued that in general terms, the experience of value of an object can be influenced by the strength of the attentional and affective engagement with that object. For empirical aesthetics, this value can be assessed by measuring the subject's subjective responses, liking, aesthetic quality, etc., or their psychophysiological responses, GSR, ECG, etc. This is because engagement strength is said to be accompanied by the feeling of a motivational force which will be either of attraction or of repulsion from the object. According to this view, pleasure experienced about something involves a component of motivation, which is a classical hedonic principle. This is supposedly due to the fact that people are not just reacting to a stimulus, they also assign meaning and significance to it as a function of their own current needs, desires, goals, and motives. Higgins has related the concept of engagement strength to the experience of flow as it was proposed by Csikszentmihalyi 1990. A high level of engagement strength is a prerequisite to enter that state of flow. This state has been suggested as a state of mind a spectator of an artwork enters when confronted with an artwork and successfully masters all aspects of the appreciative process and, eventually, is aesthetically moved by it. Markovic 2012. It is a type of transcendent understanding of the expressive qualities of an artwork and is related to the ultimate enjoyment of it. For this to happen, there must be an effective predisposition to let the artwork genuinely get under your skin and to engage willingly with it. Otherwise, this state of flow is not likely to be attained, irrespectively of how long a person looks at an artwork. The importance of carefully designing an experiment's instructions so that they facilitate an effective predisposition and strong engagement with the artful object, here, an art stimulus, holds for all art forms. What makes dance special in this respect is that real dance is a multisensory experience. Thus, experimenters must be skillful at transmitting 252 Juliet F. Christensen and Corinne Jola the special nature of attending a dance performance. Besides, whilst the vast majority if not all people have looked at paintings in an art gallery, or in poster shops, comparatively few people have experienced dance performances firsthand. Thus trying to instill this particular mindset in an experimental participant can be particularly challenging with dance stimuli, especially if the researcher has no own dance or dance viewing experience. 12.5 Requirements for the future. For a fruitful future of dance and science to occur, a number of points require careful consideration. When investigating cerebral processes in response to watching dance, known parameters are motion, culture, presence, and experimental instruction. We mentioned that dance needs to be considered in its complete form. How do we achieve all of this? For the design of experiments using ecological valid stimuli, there are at least 3 requirements to follow that support adequate consideration of these points. 1. The experience of the participant. 2. The knowledge of the experimenter. 3. The multisensory nature of dance. Requirement 1. Consideration of participants' sensory experiences. We have discussed the fact that the aesthetic appreciation of an experimental subject is never independent of context. We provided a detailed example of how the background on video recordings can change the context of a dance performance. Other contexts are related to time, historical context, see Gombrich 2006, location, cultural context, see Jola et al. 2012a, presentation form, i.e. duration, see Jola et al. 2011b, and presentation size, Wildschut 2010. Hence, the context of the stimuli needs careful consideration when creating the stimuli and should be described in the experimental outline. Furthermore, the participants' reported experiences when watching the stimuli offers relevant insight into the quality and appropriateness of the stimuli. Hence, we propose that subjective experiences should be collected and reported as part of any study using complex aesthetic stimuli such as dance. In other words, it is important to recognize that the aesthetic appreciation is a form of experience and thus the stimuli should be created in such a way that they first allow such an aesthetic experience to evolve, and secondly, that this aesthetic experience can be measured and reported in some way. Finally, since the context affects subjects' experience dependent on their expertise of the matter, it is highly relevant that the subject's expertise is clearly described. Requirement 2. State the background and knowledge of the researcher. It is largely those scientists who have at least a marginal interest in dance that employ dance in their studies, yet the level of expertise varies hugely. Expertise in dance is necessary to understand to at least some degree what we know about our subject of study, CEG Jola et al. 2011b. Moreover, as Gombrich makes very clear, knowledge affects what one sees, Gombrich 2006. We thus argue that not only is it relevant for the scientist to spend time investigating the human brain, but also to spend time investigating the stimuli used, a practice described as embodied neuroscience, Jola 2010. In addition, we argue that it would be beneficial if the scientist's approach to dance were made transparent by citing a clear definition of terms, especially that of dance, at the very least. Moving towards ecological validity and empirical aesthetics of dance 253 Requirement 3, investigating the multisensory nature of dance. Aesthetic experience is based on visual perception, as in visual form of art, can evoke various forms of sensory experiences, kinesthetic, tactile, etc. As we have outlined in this chapter, the aesthetic appreciation of dance is a sensory experience that touches different sensory modalities, not just the visual or kinesthetic sense. It is thus crucial to improve our understanding of what forms of sensory experiences dance can evoke, particularly as different forms of dance supposedly evoke different forms of sensory experiences. Furthermore, we believe that these different sensory experiences can be very subtle and are only evident if the dance is presented in its natural, multisensory form. CEG Jola ETAL 2014 dance is often performed to music, with audible footsteps and breathing, seeing dancers sweat, etc. Hence, this is why ecological valid forms of dance stimuli are crucial. Dance needs to speak to us to be appreciated, otherwise it is a condensation of purely physical motion. Therefore, a definition of dance underlying the selection of the dance stimuli of a study may be helpful. 12.6 Conclusion. In many instances, the scientific employment of dance does not live up to the natural phenomenon of dance. As outlined earlier, a number of studies have shown evidence that the way one presents dance affects perceptual, cognitive, and evidently neuronal processes significantly. Therefore, we argue for a protocol of necessities when using dance as a performative art form in studying the human brain and human behavior. We consider it crucial to use genuine dance, dance that can be seen and enjoyed watching on stage or in other aesthetic contexts. Hence, it could be presented in the form of static displays, photographs, video clips, or live performances. Due to the multifaceted nature of dance, its complexity should be recognized and acknowledged in order to reach ecological validity. In other words, the dance should be seen as dance by experienced spectators. For this, qualitative data should be collected and reported not only from participants, but optimally also from dance experts specifically consulted for the study. These reports should include the overall experience of the experiment, appreciation of the stimuli, and a description of what participants think they saw in the experiment. All stimuli used should further be made available to readers, online, or by request. Parameters of the dance strands should be analyzed and/or described, and these are motion, gestural components, and a description of the dance form used. We want to encourage researchers in empirical aesthetics as well as in general, to define more thoroughly what they mean by dance when using dance stimuli, 2, to design their stimuli according to a theory of what dance is that also bears the scrutiny of dance experts. Only in this way can one be certain to test the responses to the real thing, and finally, 3, to embed their studies in the general framework of empirical aesthetics. Using dance as a stimulus, in our view, involves a commitment, thus conclusions drawn from results obtained with not carelessly designed dance stimuli are based on shaky grounds. The difficulty for the scientist resides especially in understanding what exactly makes dance dance, and not just a motor pattern. What if the enhanced motor response found so often 254 Julia F. Christensen and Corinne Jola in experts when they watch, impoverished, dance movements of their area of expertise is not due to the much suggested enhanced motor simulation, but rather due to the dancer's compensatory cognitive and neural mechanisms trying to make up for the pitfalls of the movements they see. To fulfill these criteria, we propose cross-disciplinary collaborations. The existing understanding of dance by dance practitioners, choreographers, scenographers, as well as dance scholars, i.e. humanities, philosophy, phenomenology, and languages, is useful in the study of the aesthetic experiences of watching dance. Furthermore, collaborations with other scientists working in specific areas of perception, cognition, physiology, and computation are hugely beneficial in order to control for parameters of the strands of dance. Empirical aesthetics began with the aesthetic experiences in response to visual art. The frameworks were based on models of visual perception. These are only partially applicable to the study of aesthetic experiences when watching dance. Although dance is perceived visually, the sensory experiences clearly extend beyond the visual sense. Kinesthetic responses are important and so are auditory experiences, as dance is often accompanied by music or physical sounds. One could even argue that dance evokes tactile sensory aesthetic experiences through the observation of the touch and interaction between dancers on stage. Dance has come late onto the map of experimental cognitive psychology and neuroscience. This is why the models provided by these fields may not yet be conclusive or encompassing for dance, but as shown here, provide a good starting point. Chapter 13 Liking music, genres, contextual factors, and individual differences. Kathleen A. Corgal and E. Glenn Schellenberg. 13.1 Introduction. The amount of time and money that people spend on music provides ample evidence that listening to it is important for most of us. We choose to listen to music at concerts, on the radio, and on portable media players, e.g. MP3 players, computers, and CD players. We also hear music that others choose for us in television shows and movies, in shopping centers and restaurants, and at significant events such as weddings and funerals. In 2012, the International Federation of the Phonographic Industry, 2013, reported that global revenues from digital sales alone, i.e. not including CDs or vinyl, reached approximately $5.6 billion, which confirms that music is valued worldwide. The amount of resources devoted to music consumption establishes unequivocally that at a fundamental level, people enjoy listening to music. However, different individuals like different kinds of music, and the same individual may exhibit greater or lesser appreciation for a particular genre or piece of music depending on the circumstances in which it is heard. The goal of this chapter is to provide an overview of research that has examined preferences for genres and liking individual pieces of music. Over the past few decades, research interest in music perception and cognition has grown. Jones et al. 2010, as has interest in emotional responses to music. Jesslin and Sloboda 2010. Nevertheless, research on liking or disliking music, the most basic emotional response, has received relatively little attention. For example, Jesslin and BHKLL 2008 proposed several mechanisms to explain why listeners respond emotionally to music, but they did not consider basic liking. Instead, they focused on how music evokes emotional responses such as happiness or sadness, ignoring the fact that responding emotionally to music occurs on two levels. Hunter and Schellenberg 2010. One is evaluated whether the listener likes the music or considers it to be good. The other level is the specific feeling, such as happiness, that is expressed and/or evoked. In the present chapter, our focus is on the evaluated level. What makes someone like a particular song or genre of music? How are individual differences related to music preferences? What factors influence how liking music develops or changes? Our goal is to provide an overview of what is known and unknown in response to these questions, focusing primarily on studies published since 2000. 264 Kathleen A. Corgal and E. Glenn Schellenberg. 13.2 Liking different genres of music. Most research on music preferences has focused on characterizing the kinds of people who like different genres of music, e.g. pop, rock, country, rap/hip-hop, classical, jazz, etc., asking whether individual differences in demographic, cognitive, and personality variables are correlated with how much a person likes particular genres. Although the concept of genre may seem poorly defined, genres can be immediately obvious to the average listener. In one instance, college freshmen registered in a psychology course performed at above chance levels on a genre identification task after hearing excerpts of music that were only 250 milliseconds in duration. Jurgen and Perrault 2008. Because recognizing and classifying genres can be virtually instantaneous, genres are likely to play an important role in evaluative responses to music. Early research tended to focus on documenting positive associations between preferences for genres, particularly music that sounded aggressive or negative, and personality characteristics such as rebelliousness or sensation-seeking. Arnett 1992, Carpentier et al. 2003, Cattell and Saunders 1954, Christensen and Peterson 1988, Dollner 1993, Glasgow et al. 1985, Hakanen and Wells 1993, Hansen and Hansen 1991, Little and Zuckerman 1986, McNamara and Ballard 1999, Payne 1980, Rawlings and Carly 1997, Rawlings ETAL 1995, 2000, Rowe 1985, Schwartz and Fouts 2003, Weaver 1991, Wheeler 1985, C. Renfro and McDonald 2010 for a review. More recently, researchers have begun to study associations between genre preferences and personality more comprehensively. 13.2.1 The structure of music preferences Renfro and Goslings, 2003. Research was the first to examine systematically the underlying structure of music preferences and whether these preferences are associated with contemporary personality constructs. The Big Five, McRae and Costa 1987. The Big Five considers individual differences in personality to vary according to 5 major dimensions: openness to experience, conscientiousness, extroversion, agreeableness, and neuroticism, forming the acronym MOTION. In a series of studies, Renfro and Gosling examined links between genre preferences in the Big Five as well as other personality, demographic, and attitudinal variables. Rather than using judgments made by the researchers to select which music genres to include, a preliminary study established participants' familiarity with various genres and subgenres. The authors used these data to create the short test of music preferences, STOMP, a list of 14 genres that were familiar to most college students in the United States. The STOMP requires participants to provide a rating from 1, dislike strongly, to 7, like strongly, for each genre. In different samples that comprised thousands of participants from different geographical regions in the USA, Renfro and Gosling measured music preferences with the STOMP, as well as by analyzing participants' online music libraries. These analyses allowed them to determine 1. Whether fans of a particular genre, such as rock, also tend to be fans of other genres, such as alternative or heavy metal. 2. How many truly independent dimensions of preferences there are, and 3. Whether liking particular genres varies systematically with other non-musical differences among individuals. Liking music 265 principal components analysis revealed 4 main factors, i.e. latent variables, of music preferences, Renfro and Gosling 2003. The first, which the authors designated reflective and complex, represented preferences for classical, jazz, folk, and blues, genres that were also considered to be more musically complex than other kinds of music even though the blues in particular usually has a very simple harmonic structure. In any event, liking these genres was associated positively with openness to experience and liberal political views. It was also associated positively with self-reports of intelligence, but negatively with self-reports of athletic ability. The second factor, intense and rebellious, described preferences for rock, alternative, and heavy metal music. These preferences were also correlated positively with openness to experience and with self-reports of intelligence and athletic ability. Fans of upbeat and conventional genres, which included pop, soundtracks, religious, and country music, tended to be extroverted, agreeable, conscientious, and politically conservative. They also considered themselves to be physically attractive and athletic, but they scored low in openness to experience. The fourth and final factor, energetic and rhythmic, reflected preferences for rap/hip-hop, soul/funk, and electronica/dance music. Liking for these genres was correlated positively with extroversion, agreeableness, and political liberalism, and with self-reports of attractiveness and athletic ability. In a series of follow-up studies, Renfro and his colleagues showed that people easily form impressions about fans of different music genres that are stereotypical but are nonetheless often quite accurate. Renfro and Gosling 2006, 2007, Renfro ETAL 2009. These findings are consistent with the idea that music preferences are an important part of an individual's identity, and that such preferences can communicate important information about a person's personality, values, and lifestyle, e.g. North and Hargreaves 1999. Other research suggests that similarities in music preferences between individuals are considered to reflect a common value system, which in turn provides a basis for social attraction, for ETAL 2011. In some instances, studies conducted in countries other than the United States have found results similar to those of Renfro and Gosling, 2003, concerning the underlying dimensional structure of music preferences. For example, Langmeyer and colleagues, 2012, replicated and extended Renfro and Gosling's results with a sample of young German adults. The results validated the 4-factor structure of music preferences using real audio samples of popular songs that exemplified the relevant genres instead of a paper-on-pencil questionnaire. Nevertheless, results from many other studies differed from the original findings. For example, in another German sample with a wider age range, a 6-factor structure was obtained, Schaefer and Siegelmeier 2009. In a large sample of Dutch adolescents, moreover, a 4-factor structure of music preferences emerged, but some genres were attributed to different character traits than in the American samples, specifically those that were either more techno/trance or less gospel, popular in the Netherlands than in the United States. Delsing ETAL 2008. In another sample of Dutch adults between 22 and 60 years of age, Dunn and colleagues, 2011, found that a 4-factor structure explained underlying music preferences, but attribution of the individual genres onto the attributes meant that the factors needed to be 266. Kathleen A. Cordell and E. Glenn Schellenberg defined differently than in the original study. Renfro and Gosling 2003. One factor represented traditional musical genres, classical, folk, blues, country, religious. Another represented harder rock genres, rock, alternative, heavy metal. A third represented genres in which rhythm plays a major role, rap, dance, soul, jazz, and the fourth represented softer rock genres, pop, soundtracks. The fact that a preference for classical and for country music was seen to belong to the same factor is particularly noteworthy, and as one might expect, the diverse nature of jazz music, e.g. Diana Krall and Ornette Coleman are both jazz artists but they sound very different, meant that liking jazz was associated with more than one factor, i.e. also with traditional genres and soft rock. Colley, 2008, found that the structure of British undergraduates' music preferences was similar to that of Renfro and Gosling's, 2003, American samples, but with some additional gender differences. Female students exhibited greater liking than male students for top 40 pop music, but males showed greater liking for hard rock. In a Canadian study, an 8-factor structure emerged when participants provided liking ratings for 30 different genres instead of the 14 from the STOMP, George ETAL 2007. The sample comprised many undergraduates from a Christian college as well as adults from the surrounding area who also tended to be quite religious. As a consequence, participants provided ratings for 4 different genres of Christian music, and 2 of these loaded onto one factor, called Christian Contemporary, and 2 loaded onto a different factor, Traditional Christian. The clearest non-musical individual differences were evident for the factors labeled rebellious, alternative, classic rock, grunge, heavy metal, punk, rhythmic and intense, hip-hop/rap, pop, reggae, rhythm, and blues, and classical, choral, classical instrumental, Disney/Broadway tunes, opera/ballet, piano. Greater levels of liking for genres that belonging to the rebellious or rhythmic and intense factors were evident among participants who were younger, underemployed, less educated, and less spiritually minded. These individuals also tended to have poorer social skills, higher levels of neuroticism and hostility, and lower levels of self-esteem, conscientiousness, and agreeableness. People who liked genres that loaded onto the classical factor showed essentially the opposite pattern. Brown, 2012, asked university students in Japan to provide liking ratings for 12 different genres, 6 of which were taken from the STOMP. 6 others were included because they were relatively well known to Japanese listeners. A 4-factor structure was revealed that closely resembled Renfro and Gosling's, 2003, original findings, and participants with high scores on openness to experience tended to exhibit greater liking for so-called reflective and complex music. In another study conducted in Japan, however, the original STOMP led to a 4-factor structure but several genres loaded onto factors different from those in the original study, Oshio 2012. Even Renfro and his colleagues have found that the dimensional structure of music preferences differs from the solution they reported initially. In a series of follow-up studies, they asked listeners to provide liking ratings for many, i.e. 25 to 94 depending on the particular study, 15-second excerpts of music taken from unfamiliar recordings that represented 26 different genres, Renfro ETAL 2011. As in the study undertaken by Langmeyer and colleagues, 2012, instead of making liking ratings for genre labels, participants made liking music 267 ratings for actual music. A separate group of participants made 14 ratings about each excerpt, 7 based on musical descriptors, dense, distorted, electric, fast, instrumental, loud, percussive, and 7 based on psychological descriptors, aggressive, complex, inspiring, intelligent, relaxing, romantic, sad. Principal components analysis revealed that liking ratings varied along 5 distinct dimensions rather than 4, which were labeled so that they formed the acronym music: mellow, unpretentious, sophisticated, intense, contemporary. The authors explained loadings onto the particular dimensions as a function of the different genres and the average ratings for the 14 descriptors. Renfro et al. 2011. Mellow music was judged to sound slow, soft, romantic, relaxing, and non-aggressive, and the excerpts belonged primarily to soft rock, R&B/soul, and adult contemporary genres. Unpretentious music was vocal, non-distorted, soft, non-aggressive, and simple, and the excerpts came from country and bluegrass genres. Sophisticated music was non-electric, non-percussive, non-distorted, intelligent, and inspiring, and the excerpts were from recordings of classical and marching band music. Intense music was distorted, loud, electric, aggressive, and non-relaxing, with excerpts coming from rock, punk, and metal genres. Finally, contemporary music sounded electric, percussive, and happy, and the excerpts were primarily from rap, electronica, and Latin genres. Although the results of the study by Renfro and his colleagues, 2011, revealed that music preferences varied reliably as a function of musical attributes, as measured by the descriptors, and genre membership, genres predicted liking ratings slightly better than attributes. In a follow-up study, however, the same 5-factor, music, solution emerged when all of the stimuli were excerpts from jazz music, or all were excerpts from rock music, Renfro et al. 2012. In these instances, the underlying structure of music preferences was a sole consequence of musical attributes, i.e. differences in how the pieces sounded, rather than genre differences. Thus, music preferences involve liking for particular musical attributes as well as liking for genres, although music attributes may actually play a larger role. The music model provides a new foundation for future research that seeks to examine what makes different individuals like different pieces of music. Considered as a whole, though, the available literature suggests that the structure of underlying musical preferences differs across cultures, ages, and historical periods, because different genres are more or less popular with different groups of people. The factors, latent variables, that emerge in principal components analyses also vary depending on which manifest variables, genres, participants are asked to rate, and whether participants rate their liking for genre labels or actual excerpts from recordings. It is also clear that the researcher's own musical preferences influence how the factors that emerge are labeled, such that any dimension associated with classical music may be labeled complex or sophisticated even though the blues, marching band, or country music belong to the same factor. 13.2.2 Genre preferences and individual differences. Findings from studies of associations between music preferences and personality dimensions are more consistent, particularly for openness to experience and extroversion. In a number of studies, openness to experience was associated with preferences for elite or highbrow genres such as classical and jazz, as well as with intense and rebellious genres such as rock. Several studies have also reported links between extroversion and liking genres of music that are considered upbeat and conventional or energetic and rhythmic, including pop, rap/hip hop, and dance. By contrast, associations between music preferences and the other 3 dimensions of personality that comprise the Big Five, i.e. agreeableness, conscientiousness, and neuroticism, have been much less. A few recent studies also examined associations between more specific personality facets, rather than broad dimensions, and music preferences. For example, the dimension openness to experience comprises 6 facets: imagination, being prone to fantasy, artistic interests, appreciating poetry, art, music, and beauty in nature, emotionality, awareness of one's own feelings, adventurousness, eagerness to try new things, intellect, receptiveness to new ideas, and liberalism, readiness to challenge authority, convention, and tradition. In principle, future research could delineate personality differences between fans of classical music and fans of rock music, who both have relatively high levels of openness to experience. For example, rock fans may be more liberal but classical fans more emotional. More generally, some facets may be better than other facets as predictors of music preferences, and better than broad dimensions as well. Other scholars have examined associations between music preferences and individual difference variables other than the Big Five personality dimensions. Brown, 2012, found that liking classical, jazz, and gospel music was associated with honesty, humility, a trait that includes sincerity, fairness, greed avoidance, and modesty, which some scholars consider to be the 6th broad dimension of personality. Ashton and Lee 2008, Lee and Ashton 2008. Others have reported that men and women prefer harder and softer styles of popular music, respectively, Colley 2008, and that dichotomous thinking, i.e. black and white or all or none thinking, is associated positively with liking many genres of popular music but negatively with liking classical music, at least among Japanese undergraduates. In a more comprehensive approach with a large sample of individuals living in the UK, North, and Hargreaves, 2007A, 2007B, 2007C, reported associations between genre-based music preferences and a wide variety of lifestyle variables including income, education, living arrangements, employment, health, leisure interests, and beliefs. Listeners who liked problem music, e.g. hip-hop/rap, DJ music, dance/house, tended to hold somewhat anti-social views, although they had liberal social attitudes. They did not have particularly liberal political views in terms of taxation, healthcare, supporting recycling or use of alternative energy sources, North and Hargreaves 2007A. In general, fans of opera and classical music were more likely than other individuals to live a lifestyle associated with the upper middle and upper classes, with regard to travel, finances, education, employment, North and Hargreaves 2007C. They were also more likely to have sophisticated preferences in non-musical domains, e.g. TV and radio, reading, leisure activities, North and Hargreaves 2007B. Unfortunately, many links between music preferences and individual difference variables other than the Big Five dimensions of personality have yet to be replicated, and some of the observed associations are bound to be culture and/or cohort specific. One finding that has been replicated in several studies is a positive association between musicianship and liking classical and jazz music, whether musicianship is defined as music training or the ability to play an instrument. Colley 2008, George et al. 2007, Getz et al. 2014. An interesting avenue for future research would be to examine whether associations between music preferences and music training or any individual differences other than the Big Five personality dimensions are nevertheless explained by personality. For example, because musically trained individuals also tend to be high in openness to experience, Cordell et al. 2013, openness could explain, in part or in full, the association between music training and liking for classical and jazz music. In sum, since 2000, research has revealed much about the kinds of people who like different genres of music. One issue that has been widely acknowledged in the field is the difficulty in choosing which genres to include in empirical research and which to exclude. For example, country music is popular in America but it has significantly fewer fans in other parts of the world. As noted, the genres that are included in any study appear to influence the underlying dimensional structure of music preferences, such that solutions from principal components analysis fail to be capable of more broad generalization. In unpublished research conducted in our own lab, we administered a version of this SOMP to approximately 2,000 students registered in introductory psychology for several years in a row. The underlying factor structure differed from year to year and was never identical to that reported by Renfro and Gosling, 2003. Although researchers must ensure that the genres included in measures of music preference comprise only those that are well known in the particular culture and age group being studied, in one instance, this approach did not accurately reflect the music preferences of almost one-third of a sample of Finnish university students, Ferrer et al. 2013. In other words, measures at the level of genre may not be precise enough to capture the subtleties of many listeners' preferences. Another problem is the lack of specificity in defining musical genres, e.g. what distinguishes a rock song from a pop song, and the fact that many genres are likely to be conceptualized differently by different individuals. This issue is further complicated by the fact that genres evolve over time. Supposedly objective measures of genre such as those provided by iTunes are similarly inconsistent. For example, original studio albums by the group Radiohead are classified as alternative, yet their greatest hits collection comprising recordings from the same albums is classified as rock. In a documentary film, done ETAL 2005, and a follow-up TV series, aptly named Metal Evolution, Banger Films, in 2011, anthropologist Sam Dunn mapped a heavy metal family tree that identified the origins of heavy metal and the progression of its subgenres 270 Kathleen A. Korgal and E. Glenn Schellenberg over 40 years. Dunn's analysis of a single genre shows why it is difficult to define broad and evolving categories of music that contain distinctive subgenres that change over the years. It also shows how even within a particular genre, people often have strong opinions about their like and dislike subgenres. The non-musical social and cultural connotations associated with different genres, which also change over time, also influence music preferences. For example, rock music was associated with deviant behavior and delinquency many years ago, but it is now among the most mainstream genres in many places around the world. Finally, even within a preferred genre, some individual songs are liked better than others. It is also common to like a song that comes from a genre that one usually dislikes. In the next section, we examine what factors influence whether or not a listener will like a particular piece of music, and how such liking is associated with contextual factors and individual differences. 13.3 Liking for individual musical pieces. The study of liking individual pieces of music can include excerpts taken from a wide variety of genres or, alternatively, many different excerpts from a single genre. In either case, researchers can examine what factors influence liking responses while 1. Minimizing the influence of extra musical, social, and cultural connotations that are associated with different genres, and 2. Reducing random variation that arises from individual differences in listeners' understanding of how genres differ according to their labels. The use of unfamiliar music excerpts rather than verbal labels or descriptions minimizes the effects of episodic memories that may be associated with familiar pieces. 3.1 Liking and exposure. Anecdotally, listeners often report that they do not like a piece of music initially, even though they may grow to like it after repeated listening. Indeed, frequency of exposure, or familiarity with a stimulus, has been known to influence liking ever since the Jonks' 1968 seminal research documenting the mere exposure effect. This refers to the fact that originally neutral stimuli, e.g. line drawings, Chinese characters, are liked better when the perceiver has encountered them previously, even when the perceiver cannot remember them explicitly. Early research provided evidence that the effect extended to excerpts of unfamiliar music, which are liked better if the perceiver has heard them before. Nevertheless, people often complain that a particular song has been overplayed. In other words, listeners can come to dislike a song that they have heard too frequently, especially over a short period of time. Consistent with these anecdotal observations, some theorists have proposed that liking varies as an inverted U-shaped function of novelty. Early 1970, Stang 1974. Completely unfamiliar stimuli are potential threats and therefore somewhat disliked. With initial exposure that has no negative consequences, liking increases because the stimulus is more predictable and less of a threat. As exposure liking music 271 increases further, however, the stimulus can become too predictable, i.e. boring, such that liking decreases. Early research provided evidence consistent with the proposal that overexposure to music decreases liking. Bartlett 1973, Brenter et al. 1994, Getz 1966, Hargreaves 1984, Hayden 1975, Berber et al. 1933. In the real world, music listening occurs in a context. In a typical experimental setting, the listener is asked to attend closely to the music stimuli, usually while providing some kind of rating or judgment. Although everyday music listening can be equally focused, such as during a concert, it frequently occurs under more passive or incidental listening conditions. For example, music is often present in the background while people drive, shop, do housework, cook, surf the internet, watch television, and exercise. In these contexts, attention is divided between music listening and the task at hand, and familiarity with the music may develop more slowly. As such, one important question is whether the effect of exposure on liking varies under different listening conditions. To answer this question, Spunner and colleagues, 2004, Experiment 2, presented listeners with excerpts from concerti, i.e. orchestral music with a featured lead instrument, twice, 8 times, or 32 times under one of two conditions. In the focused listening condition, participants actively attended to the excerpts because they were required to identify the lead instrument in each presentation. In the incidental listening condition, listeners listened closely to a narrated story presented in their right ear while the music excerpts were presented at a low volume in their left ear. The results revealed an inverted U-shaped function of liking as a consequence of exposure for focused listeners, with liking increasing from baseline, no previous exposure, up to 8 presentations, and then decreasing down to baseline levels with 32 exposures. By contrast, in the incidental listening condition there was a linear increase in liking as a function of exposure. These findings reveal that familiarity with a piece of music increases liking for it, up to the point at which it becomes too familiar. Such overfamiliarity occurs only, or at least more quickly, when listeners are attending closely to the music rather than overhearing it playing in the background. Frequency of exposure may also affect liking differently across individuals, as a consequence of differences in personality or other variables. In one study, Hunter and Schellenberg reanalyzed the data from the focused listening conditions of 2 previously reported experiments, Schellenberg et al. 2008, Spunner et al. 2004, Experiment 2. As a group, participants exhibited an inverted U-shaped pattern of liking as a function of exposure frequency, as reported in the original published articles. When participants were examined individually, however, less than half of them actually exhibited this pattern. The other participants exhibited monotonic increases, monotonic decreases, or an upright U pattern of liking with increasing exposure. To examine whether personality can explain such individual differences, Hunter and Schellenberg, 2011a, replicated the findings from the focused listening condition from Spunner and colleagues, 2004, Experiment 2, but they also included a measure of the Big 5 personality dimensions. Compared to individuals who were low in openness to experience, individuals who scored high in this dimension liked novel musical excerpts more and excerpts they had heard repeatedly less, showing particularly rapid satiation at 272 Kathleen A. Korgal and E. Glenn Schellenberg, a function of exposure. Moreover, although the inverted U-shaped pattern for liking was common among listeners who scored low in openness, the most common pattern for listeners who scored high in openness was a monotonic decrease in liking with increasing exposure. This finding was expected because a hallmark of openness to experience is a preference for variety over routine. In sum, the effect of exposure on liking interacts with a variety of other factors including initial liking, the listening context, and personality. Other factors that are likely to influence how quickly an individual will tire of hearing a particular song can be difficult to test in a laboratory setting. For example, we do not typically hear the same musical excerpt multiple times in one day, let alone in 1 hour, which can be the case in an experiment. One would expect it to take longer for listeners to dislike an overplayed song if the exposures were spread out over days or weeks compared to when they occur repeatedly in a short time frame. Another factor that interacts with the effect of exposure on liking is how much the excerpt of music is liked initially. Repeatedly playing a song that a listener dislikes strongly is unlikely to shift such displeasure in a positive direction. In one study, listeners heard 12 excerpts of unfamiliar orchestral music 6 times each, with Liet and Branagh 2007. They rated how much they liked each piece after they heard it the first time, and again after they heard it the 6th time. The 12 pieces were pre-selected so that half sounded pleasant, i.e. with positive valence, and the other half sounded unpleasant, negative valence. As in many other studies, e.g. Hunter et al. 2008, 2010, 2011a, 2011b, Hassan et al. 2002, Talfa et al. 2008, Ledenite and Schellenberg 2012, Schellenberg et al. 2008, Thompson et al. 2001, Bayard et al. 2008. These adult listeners initially preferred positively valenced over negatively valenced music. After repeated exposure to both types of music, however, responses became more polarized. Positively valenced excerpts were liked even more, but negatively valenced excerpts were liked even less. It is unknown whether liking for the unpleasant sounding music increased initially, i.e. between the first and sixth exposures, before it began to decrease. The idea that music liking peaks after a moderate number of exposures raises the possibility that moderation in general may be fundamental to liking. Berlin, 1970, also proposed that liking should exhibit an inverted U-shaped function according to complexity. In the case of music, it will be like most when its melodic, rhythmic, and metrical structures are not too simple, predictable, and uniform, nor too surprising, unpredictable, and erratic. Using piano pieces composed specifically for experimental purposes, Haydu, 1975, found evidence consistent with this view. His participants preferred pieces that exhibited moderate levels of complexity, i.e. those that made use of a moderate number of different chords and a moderate amount of rhythmic syncopation, over pieces that were either too simple or too complex. These results have also been replicated with more ecologically valid stimuli. For example, when listeners were asked to rate unfamiliar excerpts of New Age and house music in terms of liking and subjective complexity, they showed a similar preference for excerpts with moderate complexity, North and Hargreaves 1995. Nevertheless, the effect of complexity on liking may not be uniform across all genres of music. For example, Orr and Olson, 2001, presented listeners with jazz and bluegrass improvisations that were created by professional musicians to vary in complexity. For bluegrass excerpts, listeners exhibited a clear preference for a moderate level of complexity. For jazz excerpts, however, they preferred simplicity. It is possible that the inclusion of even simpler jazz improvisations may have revealed increases followed by decreases in liking as complexity increased. It is also possible that the effect of complexity on liking differs across genres, or that other factors such as initial liking or general familiarity with the genre interact with the effect of complexity on liking. Moreover, complexity may not influence liking for all music listeners. Orr and Olson, 2005, found that the effect of musical complexity on liking was weaker or non-existent among professional and amateur musicians compared to individuals with no music training. The authors suggested that musically trained individuals use a different set of criteria in their aesthetic judgments compared to other people, placing less importance on complexity. There is also some evidence that preferences for simple or complex music are affected by situational factors. For example, in one study, listeners preferred to hear simple music in the background while they performed a difficult sensory-motor task, but they preferred complex music while they performed a simple task. Arx et al. 1986. Thus, the preferred level of musical complexity may vary with an individual's attentional capacity to process the music at a given point in time. 13.3.3 Liking and feelings. One of the most common reasons that people give for listening to music is because of the way that it makes them feel, or because it can change how they are currently feeling. Jesslyn and Laha 2004, Lonsdale and North 2011. In other words, emotional responding on the evaluated level can be influenced by responding on the feeling level. When Jesslyn and Laha, 2004, analyzed listeners' 3 responses to the question, why do you listen to music? The most common response, 47%, was to express, release, and influence emotions, followed by other emotion and liking-related reasons such as to relax and settle down, because it makes me feel good, because I like/love music, and to get energized. Other research confirms that people particularly enjoy music that evokes intense feelings. Leninite and Schellenberg 2012, Schellenberg et al. 2012. One especially strong positive response to music is the physical sensation of chills, or thrills, Goldstein 1980. Chills are described as shivers down the spine, or a tingling sensation that is usually felt at the back of the neck and often accompanied by goosebumps. In the first study to describe these kinds of physical responses to music, approximately half the participants reported experiencing music-induced chills, Goldstein 1980. Subsequent research revealed that individuals who are high in openness to experience tend to experience chills more frequently than other individuals. McRae 2007, Nussbaum and Sylvia 2011, Sylvia and Nussbaum 2011. Although chills can also occur in response to other stimuli, including visual art, tactile stimulation, think of a feather tickling the back of your neck, and even fantasies or memories, chills elicited by music tend to be experienced as 274 Kathleen A. Cordell and E. Glenn Schellenberg particularly pleasant, Goldstein 1980, Brew et al. 2011, Hanks 1995. There is also some evidence that individuals tend to experience chills in response to unexpected or surprising musical events, such as an unexpected harmony or a sudden change in volume or orchestral texture, e.g. Brew et al. 2007, Gunn et al. 2007, Hanks 1995, Sloboda 1991. Because chills are indicative of peak emotional experiences, pieces that elicit chills tend to be accompanied by higher ratings of the intensity of the listener's emotional response, faster heart rate, and a more intense skin conductance response, Brew et al. 2009. Chills also tend to occur more frequently in response to emotionally expressive music compared to relaxing or arousing music that is less emotionally expressive, Ricard 2004. Chills most often occur in response to familiar and well-liked music, Brew et al. 2009, possibly because familiar music is more likely than unfamiliar music to induce powerful emotions. Consistent with the view that chills represent particularly emotional experiences, several studies have shown that music-induced chills are associated with physiological arousal, e.g. Craig 2005, Brew et al. 2011, 2009, Gunn et al. 2007, Ricard 2004, Salenpo et al. 2011, 2009, as well as with activation in brain areas that are involved in reward and emotion processing, e.g. Blood and Zaderer 2001, Salenpo et al. 2011. In fact, participants' subjective ratings of the intensity of the chill response are correlated with the amount of dopamine released in the nucleus accumbens, also known as the brain's pleasure center, Salenpo et al. 2011. In short, results from behavioral, physiological, and neuroimaging studies confirm that chills are particularly strong, positive emotional experiences to well-liked music, and, conversely, that well-liked music often tends to be music that influences how the listener feels. 13.3.4 Liking and specific feelings. Listeners tend to experience positive emotions more frequently than negative emotions in response to music, e.g. Gabrielson 2001, Jesslyn and Laha 2004, Jesslyn et al. 2008, and they generally prefer music that expresses positive emotions such as happiness over music that expresses negative emotions such as sadness, e.g. Hunter et al. 2008, 2010, 20118, B, Hassan et al. 2002, Kalfa et al. 2008, Leninite and Schellenberg 2012, Schellenberg et al. 2008. Thompson et al. 2001, Viard et al. 2008. This preference for music that is positive and balanced is evident even among individuals who have experienced damage to the emotion processing centers of the brain, including the amygdala, Gosselin et al. 2005. Thus, the elicitation of positive emotions appears to be central to the universal appeal of music. At the same time, we know that people often listen to sad-sounding music. But why would people choose to listen to sad-sounding music? And when in development does the preference for happy-sounding music emerge? In one developmental study, adults and 5, 8, and 11-year-old children were asked to rate how much they liked short excerpts of music, Hunter et al. 2011b. The excerpts were chosen to sound unequivocally happy, sad, scary, or peaceful. These particular emotions vary on 2 dimensions that are relevant to emotion research, arousal and valence, Russell 1980. Arousal refers to activation or energy level, whereas valence refers to pleasantness. Happiness has high arousal and positive valence, sadness has low arousal and negative. Liking music 275 valence, fear has high arousal and negative valence, and peacefulness has low arousal and positive valence. Adults showed a preference for excerpts with positive valence, happiness and peacefulness, but arousal did not influence their liking ratings. By contrast, children of all ages had elevated levels of liking for excerpts that expressed high arousal emotions, happiness and fear, but valence did not matter. Because musical tempo, fast or slow, is associated with arousal, whereas mode, major or minor, is associated with valence. Hassan et al. 2002. These results point to a basic preference for faster music in childhood, which turns into a preference for major key music in adulthood. Other findings from the same study revealed a preference for music with positive valence among female listeners, which is likely to be related to the female preference for top 40 music discussed earlier, Colley 2008. The children and adults in the study by Hunter and colleagues, 2011b, were also asked to identify which of the four emotions each excerpt conveyed. Young girls were better than young boys at this task, but both genders performed as well as adults by the time they reached 11 years of age. Among children of all ages, individual differences in identification accuracy were associated with liking. Greater accuracy predicted higher levels of liking for positively balanced music among the 5 and 8-year-olds, but lower levels for the 11-year-olds. In other words, as 11-year-olds became more accurate at identifying music as happy, sad, scary, or peaceful sounding, they also tended to dislike music that sounds happy or peaceful, that is, music their parents, particularly their mothers, like. The phenomenon of liking sad-sounding music, which has been documented empirically, Garrido and Schubert 2011, Kawakami et al. 2013, Kreutz et al. 2008, Waskowski and Rolla 2012, Waskowski et al. 2012, Zentner et al. 2008, is particularly interesting for psychologists because it demonstrates that music that expresses a negative feeling can nevertheless be evaluated positively. In fact, although sad-sounding music may be perceived to sound tragic, it can simultaneously decrease tragic feelings but increase romantic and blithe feelings, Kawakami et al. 2013. But when, where, and why do individuals enjoy listening to music that expresses a negative emotion? One factor that matters is the emotional character of previously heard songs. Schellenberg and colleagues, 2012, collected emotion intensity and liking ratings of excerpts of classical piano music that expressed happiness or sadness unambiguously. Happy-sounding excerpts were in a major key with a fast tempo. Sad-sounding excerpts were minor and slow. For each participant, one of these emotions was designated as the background emotion and the other as the contrasting emotion. Excerpts that expressed the contrasting emotion were presented after a varying number of different excerpts that expressed the background emotion. For example, some of the listeners heard a happy-sounding excerpt after hearing 1, 2, 4, or 8 different excerpts that sounded sad. Others heard a sad-sounding excerpt after hearing 1, 2, 4, or 8 different excerpts that sounded happy. As the presentation frequency of the background emotion increased, emotion intensity and liking ratings decreased, such that there was greater appreciation and more intense emotional responding for excerpts that conveyed the contrasting emotion. In other words, sad-sounding music is appreciated more after listeners have been 276 Kathleen A. Korgal and E. Glenn Schellenberg inundated with happy-sounding music, and vice versa, because it represents a change from emotional monotony. Other research suggests that sad-sounding music may be liked more after listeners are fatigued or in a negative mood. Schellenberg and colleagues, 2008, collected liking ratings of musical excerpts that expressed happiness or sadness after they had been heard 0, 2, 8, or 32 times previously. Half the participants heard the music in a focused listening condition, which required them to identify whether each excerpt expressed happiness or sadness. The other half incidental listeners completed the same task used by Spunner and colleagues, 2004, while the music was presented softly in the background. Specifically, they heard a narrated story in their right ear and were required to press one button every time they heard the word and, another button every time they heard the word bid, and to count the number of times they heard the word bud. In their left ear, the happy and sad-sounding excerpts were presented audibly but very quietly. Exposure frequency has the usual effect on liking. For focused listeners, liking first increased but then decreased as the number of exposures increased. For incidental listeners, liking increased linearly for excerpts heard more frequently. But there was also an interaction between listening condition and emotion that was independent of number of exposures. Focused listeners exhibited the typical bias, liking happy-sounding more than sad-sounding excerpts. For incidental listeners, however, sad-sounding excerpts were liked just as much as happy-sounding excerpts. Importantly, this difference was driven by greater liking for sad-sounding pieces in the incidental compared to the focused listening condition. Why was sad-sounding music liked more for some listeners? Schellenberg and colleagues, 2008, suggested that the difficult and attention-demanding task for incidental listeners may have affected their emotional state negatively. After completing the task, participants may have been fatigued or even slightly agitated, such that they found the sad music to be calming. Alternatively, participants may have displayed a mood congruency effect, preferring negatively balanced music because it matched their negative mood. To test the second hypothesis, Hunter and colleagues, 2018, induced a sad, neutral, or happy mood in participants by asking them to rate and describe how different pictures, e.g. a birthday party for happy, a building for neutral, an injured animal for sad, made them feel. Participants were subsequently presented with either a happy or sad-sounding excerpt, Hunter et al. 2018, Experiment 1, and asked to judge how much they liked it. The results revealed that although the typical preference for happy-sounding music was present after a happy or neutral mood was induced, it disappeared when listeners were in a sad mood. Sad listeners liked happy and sad-sounding excerpts equally. In a second experiment, sad moods were found to increase the perception of sadness in neutral-sounding music. These findings extended the results of the study by Schellenberg and his team, 2008, by showing that mood congruency influences what music people like in their perception of emotion in music. In short, the expression misery loves company extends to music listening. But why are people more inclined to appreciate sad music when they are in a sad mood? Is it because they prefer to listen to music that expresses their current feelings, or is it because they feel that listening to mood incongruent, i.e. happy, music would be inappropriate or ineffective at lifting their mood? Friedman and colleagues, 2012, Experiment 3, explored participants' motivations for listening to music that expressed different emotions after inducing a happy, neutral, or sad mood. Participants first generated a short list of their favorite happy and sad songs. After watching a film clip for the purposes of mood induction, they were then asked to rate 1. Their desire to listen to happy or sad-sounding songs, 2. How listening to happy or sad songs would make them feel, and 3. How appropriate it would be to listen to happy or sad songs. The results revealed that participants who were in a happy mood were averse to listening to sad-sounding music, and participants who were in a sad mood were averse to listening to happy music. The neutral group was not averse to either. Participants in a happy mood believed that listening to sad songs would worsen their mood, whereas those in a sad mood reported that listening to happy-sounding music would feel inappropriate or wrong, which would, presumably, counteract any emotion contagion effects of happy music. In some instances, then, an appreciation for sad-sounding music while in a sad mood is better described as an aversion to happy-sounding music. Other studies have examined whether individual differences based on personality or musical expertise help to explain why some people like to listen to sad-sounding music. In one study, Lidenike and Schellenberg, 2012, presented listeners with unfamiliar excerpts of music taken from a wide variety of genres. The excerpts varied in tempo, fast or slow, and mode, major or minor, such that half were obviously happy or sad-sounding, fast major or slow minor, respectively, and half contained mixed cues to happiness and sadness, fast minor or slow major. Participants first completed a background questionnaire that assessed their scores on the Big 5 personality traits and how much music training they had received. They then listened to each excerpt and rated how much they liked it, how intense their emotional response was, and which emotion, they felt. Liking for music that conveyed happiness did not differ from individual to individual. By contrast, liking for music that conveyed sadness or mixed happiness and sadness was influenced by personality and music training. Individuals who had a stronger appreciation for sad-sounding music tended to score low on extroversion, or high on introversion, and high on openness to experience, whereas individuals who enjoyed music with mixed cues to emotion tended to have more music training. Future research could examine whether introverts like sad-sounding music because of its slow tempo. We know that tempo is associated with the arousal dimension of emotion, Hassan et al. 2002, and that introverts tend to avoid excitement and activity, McRae and Costa 1987, possibly because their optimal level of arousal is relatively low, Eisent 1981. Introverts also tend to experience positive emotions less frequently than extroverts, Matthews et al. 1990, which may explain their greater appreciation for sad-sounding music. As for individuals who are high in openness to experience, their aesthetic sensitivity and preference for variety, Costa and McRae 1992, may explain why they like sad-sounding music. More specifically, these individuals may be more likely to perceive the beauty of music that expresses sadness and emotions other than happiness. Finally, Lidenike and Schellenberg, 2012, suggested that musically trained individuals have 278 Kathleen A. Korgal and E. Glenn Schellenberg a propensity for enjoying music with mixed cues to emotion because they are more sophisticated listeners. In other words, musically trained individuals may be more likely to perceive nuanced and subtle emotions in music with mixed cues, leading them to appreciate it for its emotional complexity, even though they may not care much about musical complexity. Or in Olson 2005. Other reports substantiate the association between openness to experience and liking sad-sounding music. Waskowski and Rolla 2011, Waskowski et al. 2012, and show additionally that empathy is associated positively with experiencing intense emotions in response to music and with enjoying sad-sounding pieces. Waskowski et al. 2012. Formal hypotheses about why particular groups of individuals are more likely than others to appreciate sad-sounding music have yet to be developed or tested empirically. At a more macro level, there is evidence that among the American music-buying population, liking sad-sounding and emotionally ambiguous music has become more common over the years. When Hunter and colleagues, 2008, were choosing their stimulus excerpts, they were surprised to discover that it was relatively difficult to find recent recordings that were clearly happy-sounding, fast tempo and major mode. To examine whether there has been a shift away from unambiguously happy-sounding music over the past 5 decades, Schellenberg and Von Skeeve, 2012, analyzed several musical characteristics, e.g. tempo, mode, duration, from over 1,000 songs that reached the top 40 between 1965 and 2009. In line with their hypothesis, they documented that the use of the minor mode doubled during that time, and that popular recordings became slower in tempo and longer in duration. Moreover, mean tempo decreased over time more for songs that were composed in major keys compared to songs in minor keys, pointing to a more frequent use of relatively slow tempi in music composed in major keys, but relatively fast tempi in music composed in minor keys. In short, popular music has moved away from the primarily happy-sounding songs of the 1960s, with increasing use of musical cues to sadness, slow tempo or minor mode, and emotional ambiguity, slow tempo and major mode, fast tempo, and minor mode. Even when looking beyond the level of the individual or listening context, liking for clearly happy-sounding music has decreased over the past 5 decades in American society as a whole. 13.4 Future Directions research on music preferences is in its infancy and many questions remain unanswered. Renfro and McDonald, 2010, provided a thorough review of issues in the field that have yet to be resolved, and they proposed new avenues for future research. One major limitation of the current body of work is that it focuses almost exclusively on older adolescents and young adults. Although there is some evidence that music preferences crystallize between 20 and 30 years of age, Holbrook and Schindler 1989, it is important to study how music preferences change, if at all, in middle and late adulthood, and to examine how preferences develop in the first place during infancy, childhood, and adolescence. A related issue concerns the stability of music preferences over the lifespan. In the present review, only one study examined liking music among child participants, using a cross-sectional approach, Hunter et al. 2011b. Although a few studies have examined this issue longitudinally over a few years, e.g. approximately 2-3 years, Delsing et al. 2008, Mulder et al. 2010, studies of longer duration could reveal more about whether preferences change or stay the same, especially at important transitional periods in the lifespan, e.g. from childhood to adolescence and from adolescence to adulthood. Studying music liking from a developmental perspective could provide additional insight into why music is such an important part of people's lives. 14.1 Introduction. Art forms like music, film, or literature play a major role in our cultural lives, but what exactly motivates humans to spend large amounts of their time listening to music, watching movies, or reading novels? One major incentive for consuming art is without a doubt its power to elicit strong emotions. A piece of music can move us to tears, while a painting can induce feelings of awe and fascination, a poem can evoke feelings of melancholy, elation, or joy, and a suspenseful movie can make our heart race in excitement. However, the emotional power of art leads to another conundrum. How can a piece of art evoke any emotion at all? Assuming that emotions are elicited by events that have some intrinsic significance, either favorable or harmful, to our individual concerns, or in biological terms some kind of survival value, the aesthetic emotions evoked by works of art remain largely mysterious. Unlike the imminent threat posed by the hungry grizzly bear one might accidentally run into on a hiking trip, or the feelings of excitement after having hit the lottery jackpot, the imaginary events of Romeo and Juliet, the brush strokes of Munch's The Scream, or the musical events of Mozart's Requiem seem to lack any relevance to our lives as biological organisms. So how can aesthetic emotions be integrated into a theoretical framework of human affect? What are their underlying psychological principles? And how do they relate to neural processes in the brain? In this chapter, we propose that studying patterns of tension and resolution in works of art can help to answer these questions and advance the understanding of aesthetic experience in art, and of emotions in general. Tension resolution patterns refer to the opposite poles of tension, a state of instability or dissonance associated with feelings of hopeful or fearful expectation, and its counterpart, resolution, relaxation, release, or repose. In music, for example, a sequence of dissonant chords may gradually build up tension that is finally resolved by a consonant and stable chord at the end of sequence. In literature, tension and its close relative, suspense can be created on the level of the plot, e.g. the protagonist of a novel being threatened by impending peril, as well as on more microstructural levels of the text 286 Moritz Lenn and Stefan Kolsch, e.g. a single sentence creating tension by its elaborate syntactic composition. Although tension resolution patterns are most apparent in art forms that unfold in time, e.g. music, literature, film, or dance, they can also be observed in non-temporal visual arts such as painting, sculpture, or architecture, because even in static pieces of art, the process of aesthetic experience and appreciation requires time to unfold. Fitch et al. 2009. An abstract painting, for example, can create tension by triggering a process of interpretation, a drive for understanding that is resolved when a satisfying interpretation is found. This omnipresence of tension resolution patterns in a wide variety of different art forms suggests that they play a central role in the aesthetic experience of art, motivating a closer investigation of underlying psychological principles and possible brain mechanisms. Although the opposite poles of tension and resolution were already proposed by Wilhelm Wundt as a key component of affective experience in his tridimensional theory of emotion, Wundt 1896, 1911, psychological research has largely neglected the role of tension and resolution in emotion. For rather recent considerations, see Skamack and Reisenstein 2002, Thayer 1989, Watson et al. 1999. One of our aims in this chapter is to reawaken the interest in tension and resolution phenomena as a valuable tool that may help to unravel the psychological and neural mechanisms underlying aesthetic emotions, and emotions in general. To some extent, many pieces of art can be regarded as forms of applied psychology, and Zeke, 1999, even suggests considering artists as neurologists, who creatively explore the processing characteristics of the human brain. Accordingly, tension and resolution patterns constitute an important artistic device by which artists take advantage of general principles of human cognition to evoke emotional responses. Thus, studying tension resolution patterns in works of art apart from promising new insights into the psychological mechanisms of aesthetic experience can also inform psychological and neuroscientific research on emotions evoked in non-artistic contexts. In particular, the time-varying nature of tension resolution patterns opens new research opportunities for investigating the dynamic, temporal aspects of emotional experience, thus complementing extant emotion research which mostly focuses on static aspects of brief emotional episodes. In this chapter, we explore tension resolution patterns and their relation to aesthetic experience from a psychological and neuroscientific perspective. We begin the chapter with a discussion of general psychological principles underlying tension and resolution phenomena which are relevant to a wide variety of art forms. We will argue that experiences of tension are closely related to processes of expectancy, prediction, and anticipation, and reflect a general urge to resolve dissonances or uncertainty and reach a stable state of equilibrium. We will mainly focus on temporal art such as music, film, or literature, in which tension resolution patterns are most apparent. Interestingly, these art forms also happen to have the biggest mass appeal, suggesting that they address very basic aspects of human emotion. However, many of the principles discussed also transfer to static visual art forms, e.g. painting, sculpture, or architecture. Following the general discussion of tension resolution patterns, we consider the special case of music in more detail and discuss theoretical and empirical research on musical tension. We close the chapter with considerations. Tension resolution patterns 287 on possible brain mechanisms mediating experiences of tension and resolution. Again, we mainly focus on evidence from music research. 14.2 Tension resolution patterns. Psychological principles. For a long time, writers, playwrights, choreographers, film directors, and composers have known the importance of creating tension and suspense to capture the attention of their audiences and excite emotional responses. Western classical music, for example, can be understood as a continuous flow of consonance and dissonance, stability and instability patterns of tension and resolution that orchestrate the emotional response of the listener. Likewise, tension and resolution phenomena play a key role in film and literature, and the appeal of many popular books and movies seems to directly derive from their power to evoke feelings of tension and suspense. Famous suspense movies like Psycho, Jaws, and The Silence of the Lambs have attracted millions of moviegoers, and suspenseful novels have hit bestseller lists around the world. Similarly, an abstract piece of visual art can create tension by putting the spectator in a state of incomprehension that is resolved when a meaningful interpretation has been found. Apart from works of art, various other instances in which tension and resolution phenomena play a role and potentially evoke strong emotions can be identified. In many forms of play and games, experiences of tension and resolution are important. In sports events, for example, the collective emotional reactions of spectators are often framed by episodes of tension and resolution. Similarly, tension and resolution phenomena are omnipresent in everyday life. The fearful or hopeful expectation experienced before significant life events with uncertain outcomes, or the relaxation and contentment experienced after a desired goal has been reached can all be conceived of as feelings of tension and resolution. Although these examples at first glance appear to describe very different phenomena, the common occurrence of tension resolution patterns not only in art but in virtually all aspects of human life suggests very basic underlying psychological principles, which we will explore in the following sections. 14.2.1 Uncertainty. Previously, we described tension as a state of dissonance, instability, or fearful/hopeful expectation that is associated with a yearning for resolution, that is, an urge for consonance, stability, harmony, or equilibrium. When dissecting the mechanisms by which feelings of tension or suspense are evoked, one major factor that can be identified as a mediator of tension is uncertainty, and many art forms systematically use uncertainty to evoke feelings of tension or suspense. Obvious examples are films or novels, in which uncertainty about events of the narrative plot creates suspense. In narratives, this uncertainty often takes the form of an explicit or implicit question in the mind of the reader or viewer: where was the purloined letter hidden? Who killed Laura Palmer? Etc. Such questions arouse curiosity and create the force that draws us through a narrative. Rupkin 1973. The eventual resolution of uncertainty then results in a state of understanding and provides a sense of closure that is associated with a positive affective response. The effectiveness of so-called 288 Moritz Lehn and Stephen Kolsch cliffhangers in television series provides a vivid example of the potential power of using uncertainty as a plot device, ending an episode in a moment of high uncertainty, for example, by putting the protagonist in a life-threatening situation without providing resolution as to whether he survives or not, can create a strong, almost pathological desire to watch the next episode, in which the uncertainty and the associated suspense is hopefully resolved. Uncertainty in narrative plots comes in different forms. There can be uncertainty about what will happen, when it will happen, how it will happen, or if it will happen. When Gabriel Garcia Marquez starts his novella Chronicle of a Death foretold with the sentence, "On the day they were going to kill him, Santiago Nassar got up at 5:30 in the morning to wait for the boat the bishop was coming on," there is a high level of certainty about what will eventually happen, i.e. the murder of Santiago Nassar. However, suspense is created because the exact circumstances leading to the murder, i.e. how it will happen, remain unclear, thus capturing the interest and curiosity of the reader. It may be argued that suspense in narrative plots is a very special case of tension that is only relevant to representational art forms such as films or novels, which usually refer to hypothetical events in the real world. In contrast, tension resolution phenomena in more abstract non-representational art may be based on entirely different principles. However, investigating tension resolution patterns in music, which is arguably less representational than a movie or a novel, reveals strikingly similar mechanisms. Referring to suspense in music, music philosopher Leonard Meyer states that suspense is essentially a product of ignorance as to the future course of events. Meyer 1956, p. 27. Note that in music, uncertainty about when a certain event will happen is often more important than what will happen. For example, in most pieces it is very likely that harmonic tension is eventually resolved by returning to the tonic. However, it is not clear when this resolution occurs, and many musical pieces are sophisticated examples of skillfully delaying the anticipated resolution. Likewise, abstract non-representational works of visual art can use uncertainty to evoke feelings of tension and resolution by putting the spectator in a psychological state of non-understanding that triggers a process of interpretation which may culminate in a rewarding state of resolution as soon as a sensible interpretation has been found. As noted by Fitch and colleagues, 2009, some artworks leave the tension partly unresolved, stimulating repeated viewings. Uncertainty thus works as a mediator of tension, whereas the reduction of uncertainty resolves tension. 14.2.2 Expectancy, prediction, and anticipation. Despite its importance for mediating tension, uncertainty alone is not sufficient for evoking feelings of tension. Otherwise, tension would be highest for random sequences of events that are completely unpredictable. Other key elements of tension are processes of expectancy, prediction, and anticipation. Point 3 as events unfold in time, e.g. in a piece of music, or in a narrative plot, they are constantly evaluated against a background of expectancies that are continuously updated during the temporal evolution of events. Events generating strong expectancies are then potential triggers of tension because they create tension resolution patterns. 289 An urge for resolution. To allow the build-up of tension, there is usually some temporal distance between the event generating the expectancy and the event fulfilling the expectancy, and the most effective tension resolution patterns often span large structures, e.g. the plot of a novel, or the music of an entire symphony. Importantly, in order to create tension, expected events must have some kind of significance. If the outcome of an expected event is irrelevant, that is, if it does not matter whether expectancies are fulfilled or violated, tension fails to build up. This means that expected events usually have either positive or negative valence. In narrative plots, impending danger conjures images of death or physical harm to the protagonist, which the reader hopes will be resolved by a seemingly unlikely, but highly desired happy ending. In music, tension can be driven by yearning for consonant and stable sounds that are experienced as pleasurable. In its most elementary form, tension can thus be conceptualized as a divergence between the desired goal state and the actual state of the world. This divergence between the present state and the desired goal state creates a psychological discomfort that is experienced as tension. The apparent paradox between the psychological discomfort and the feelings of pleasure derived from tension resolution experiences will be addressed later in this chapter. To make the formation of predictions possible, some kind of information or formal structure is necessary on which predictive inferences can be based. In music, the generation of predictions is afforded by the rules of a given musical system, e.g. Western tonal music. For example, certain chords bear strong implications, e.g. a dominant seventh chord tends to be followed by a tonic chord, thus creating expectancies against which subsequent events are evaluated. For an overview of predictive processing in music, see Rohrmeyer and Kolsch 2012. Musical events with a strong implicative function generating clear expectancies about subsequent events then give rise to an experience of tension. In narrative plots, expectancies can be based on genre-specific conventions, the expected happy ending of a mainstream Hollywood movie, or rules of everyday life that activate specific cognitive schemata or scripts. Bartlett 1932, Rumelhart 1980, Scant and Abelson 1977. Of course, expectancies need not always be fulfilled but can be violated to generate surprise and make a piece of art more interesting. In fact, the right mix between fulfillment and violation of expectancies is essential. If an artwork is too predictable, i.e. if it always fulfills expectancies, it runs the risk of being boring, whereas a piece of art that is completely unpredictable can easily lead to frustration by overcharging the perceiver's cognitive capacities. Of course, in some artworks, this may be exactly what the artist intended. The predictive process is relevant for generating tension and resolution in works of art built on very basic aspects of human cognition. The philosopher Daniel Dennett stated, "A mind is fundamentally an anticipator, an expectation generator." Dennett 1996. An anticipation has been suggested as a basic emotion category. Plutchik 1980. Furthermore, the ability to form predictions has been proposed as a fundamental principle of human brain functioning. Bar 2007, Ubik et al. 2010, Friston 2010, which will be discussed in more detail in the last part of this chapter. The importance of anticipation processes as a 290 Moritz-Led and Stefan Kolsch general feature of human cognition is also plausible from an evolutionary perspective because the ability to make accurate predictions about the future promotes fast and adequate behavioral responses and increases survival chances. Similarly, the urge to resolve uncertainties discussed previously has biological advantages because behavioral responses in a state of certainty and understanding usually lead more directly to a specific goal than in an uncertain environment. Thus, any art form that affords predictions and creates expectancies takes advantage of this general feature of human cognition. Likewise, the episodes of uncertainty and non-understanding that are deliberately employed in works of art to create tension address a basic psychological need for uncertainty reduction and understanding. Similar to the concept of homeostasis in biology, i.e. the tendency of biological organisms to maintain a stable state in a constantly changing environment, feelings of tension and resolution thus seem to reflect a kind of psychological homeostasis, a general tendency to resolve dissonances, conflicts, and uncertainty, and strive towards a stable state of equilibrium. Point 4. Interestingly, the fact that art takes advantage of these basic features of human cognition to arouse emotions indicates that these aesthetic emotions are not qualitatively different from the emotional experiences of everyday life, for an opposing view distinguishing aesthetic emotions from utilitarian emotions see Square 2004. Instead, the omnipresence of tension resolution phenomena suggests that the concomitant emotions build on general psychological principles that apply to a wide variety of seemingly different modalities. 4.2.3 The emotional valence of tension. Tension is associated with dissonance, instability, and uncertainty, that is emotional states that are usually associated with psychological discomfort, unease, and negative emotional valence. This raises an obvious question: why would anyone deliberately seek out experiences that are associated with tension? Works of art potentially evoke feelings of tension, yet their popularity apparently contradicts the hypothesis that tension causes psychological discomfort and should therefore be avoided. To solve this contradiction, it is helpful to distinguish between experiences of tension in art and tension in everyday life. Unlike tension experiences in real life, often considered as negative in Western societies because they are associated with physiological or psychological strain, art provides an environment in which tension can be experienced without compromising one's physical or psychological health. While tension in everyday life often induces negative emotions and is therefore generally avoided, looking for tension experiences in the arts thus provides a safeguard against potential physical or psychological harm. For a similar discussion focusing on the excitement aroused by sport events, see Lice and Dunning 1986. However, even in art, tension is often only positively valued because it is tacitly assumed that it will eventually resolve. Not resolving tension, e.g. in a movie or a piece of music, is usually experienced as unsatisfying. The pleasure derived from tension resolution experiences thus appears to be a function of the ratio between the discomfort associated with the tension and the comfort experienced during resolution. The higher the discomfort during the tension phase, the higher the pleasure in the moment of resolution. This view is also tension resolution patterns 291 expressed in Berlin's arousal jag theory, Berlin 1960, which postulates that a drop from unusually high levels of arousal that are experienced as unpleasant to a low level of arousal is associated with feelings of pleasure. However, see Zillman 1980 for an alternative account. Thus, the pleasure derived from this arousal jag is a motivator for engaging in activities that are associated with unusually high levels of arousal, such as fairground attractions or extreme sports. In a more moderate form, similar mechanisms appear to underlie the emotional reactions evoked by tension resolution patterns in works of art. 4.2.4 The paradox of repeated exposure. Previously, we discussed uncertainty in processes of expectancy, prediction, and anticipation as key factors mediating experiences of tension and resolution. This raises the question of how it is possible that tension can be experienced over repeated exposures to a piece of art. Assuming that uncertainty is resolved after the first exposure, and expectations during subsequent exposures are largely accurate, thus rendering the expectancy violations or fulfillments experienced during the first exposure ineffective, experiencing a piece of art more than once should make it dull and uninteresting. However, this contradicts common experience. The film philosopher Noel Carroll states that after having seen King Kong at least 50 times, he still feels the irresistible tug of suspense. Carroll 1996, p. 71, and a piece of music can be listened to hundreds of times while still conveying feelings of tension and resolution. Various theories accounting for this paradox of suspense, anomalous suspense, or resilience of suspense have been proposed. For the special case of narrative plots, see Brewer 1996 for an overview. These include the postulation of a willing suspension of memory, or a shift of motivation. Repeated readings of a literary text, for example, are often not motivated by evoking a state of suspense but may have other reasons such as focusing on more subtle details of the story, the writing style of the author, etc. In part, the paradox of repeated exposure may also be accounted for by imperfect memory because second exposures often occur after a period of time when considerable parts of the information of the first exposure may have been lost, and discovering what one still remembers might be a pleasurable experience. Furthermore, even if the expectancy violations and the uncertainty of the first exposure are less effective during subsequent exposures, some aspects of an artwork can create tension because they are intrinsically associated with psychological discomfort, e.g. due to sensory dissonance in a piece of music or an unpleasant image in a piece of visual art that is resistant to repeated exposures. In music, the paradox that unexpected musical events can maintain their quality of unexpectedness even after repeated exposures has been referred to as Wittgenstein's paradox, Dowling and Harwood 1986, Huron 2006. To solve this paradox, Baruchov, 1994, distinguishes between veridical and schematic expectations. Whereas veridical expectations refer to the expectations concerning actual events in a familiar piece of music, e.g. a wrong note during the performance of a familiar piece violates a veridical expectation, schematic expectations are driven by the rules of a musical system, e.g. a dominant seventh chord followed by a chord that is not the tonic violates a schematic expectation. Although 292 Moritz-Led and Stefan Kolsch veridical and schematic expectations often coincide, they can diverge in familiar pieces, in which a musical event can be veridically expected but schematically unexpected, thus accounting for the remaining experience of unexpectedness over repeated exposures. Finally, repeated exposure increases the predictive power of a listener, which might be experienced as pleasurable, and various studies have shown that repeated exposure to a musical piece increases liking. Lieberman and Walters 1968, Parrots et al. 1998, Herbert et al. 1933. This effect of mere exposure, the jump 1968, may to a certain degree compensate for the lower effectiveness of expectancy violations after repeated exposures. 4.2.5 Tension resolution patterns in the aesthetic trajectory. The aesthetic experience associated with patterns of tension and resolution can be conceived of as a trajectory that unfolds in time and comprises different temporal stages. Fitch and colleagues, 2009, proposed a minimum of 3 stages for this aesthetic trajectory: an initial stage of familiarity, recognition, or stability, a second stage of surprise, ambiguity, or tension, and a third stage of integration, resolution, or synthesis, p61. These 3 stages closely correspond to the mechanisms mediating experiences of tension and resolution described earlier. Previously we stated that the expectation and anticipation processes related to tension experiences require a formal structure that makes it possible to form predictions, that is, they presuppose some kind of familiarity and recognition reflecting the initial stage of Fitch's aesthetic trajectory. Second, the initial stage of familiarity is challenged by expectancy violations generating surprise, ambiguity, or tension. Finally, during the last stage, tension is resolved by integration and synthesis. Similar to Fitch's aesthetic trajectory, the expectation processes generating tension can also be related to different stages of the tension arc proposed by Kolsch, 2012. During the initial build-up of expectancy, tension is created. This tension may be modulated by the harmonic stability and the extent of the established structure, and further increased by breaches of expectancy generating an anticipation for resolution. When the resolution is finally reached, tension is released, giving rise to an experience of pleasure and reward. Usually, several of these tension arcs are superimposed and intertwined on different time scales, such as a phrase embedded in a part of a movement of a sonata. Kolsch's tension arc specifically refers to musical tension. However, considering the relevance of expectation processes as a general feature of human cognition, the different stages of the tension arc can also be generalized to other tension and resolution experiences. 14.3 Musical tension. The continuous ebb and flow of tension and resolution, the waxing and waning of episodes of dissonance and instability versus passages of consonance and stability is one of the hallmarks of Western tonal music, and constitutes a major aspect of emotional experience during music listening. Tension and resolution are related to various features of the music. Different notes of a musical scale are associated with different degrees of stability and instability. Different chords, or combinations of chords, convey different degrees of tension resolution patterns. 293 Consonance or dissonance. Metrical features like syncopation can delay or anticipate certain musical events, and expressive features such as dynamics and agogics create fluctuations in loudness or tempo, thus contributing to experiences of tension and resolution. Tension and resolution can be related to purely acoustic features, e.g. loudness or sensory dissonance being associated with an increase in experienced tension, Farwood 2012, Presnitzer ETAL 2000, or they can involve higher cognitive processes, e.g. expectation processes building on the rules of a musical system, Modal and Krumhansel 2007. As already mentioned, tension resolution patterns occur at different levels. They can be small scale, changing from one musical event to the next, as well as large scale, encompassing, for example, the global structure of an entire symphony. These global and local tension resolution patterns possibly interact with one another, thus maximizing the emotional effect of the aesthetic experience. As discussed previously, expectancy and anticipation processes as well as a general striving for consonance, stability, and resolution play a key role for inducing experiences of tension. The important contribution of expectation processes as a mediator of music-evoked emotions has prominently been put forward in the seminal work Emotion and Meaning in Music by Leonard Meyer, 1956, in which expectation and the associated experiences of tension and resolution were proposed as a key mechanism for creating musical meaning and emotion. According to Meyer, the continuous play with expectations in music, i.e. the fulfillment or violation of expectancies, is paramount to the associated affective and aesthetic response. Similarly, Huron, 2006, proposes a general psychological theory of expectation illustrated for the special case of music. Like Meyer, he stresses the important role of expectation for generating tension, which he defines as a physiological reaction that arises from changes in arousal and attention, in preparation for some expected event. Huron 2006, p. 305. Expectation processes in music build on the implicative structure of musical events. The dominant seventh chord, for example, is implicative of the subsequent tonic chord. For the special case of melodic expectations, Murmer, 1990, devised a theory, identifying a set of general principles mediating expectation processes and melodies, summarized in Krumhansel 1995, which have been largely confirmed by experimental research, Cuddy and Lunny 1995. Subsequent research, Schoenberg 1997, has shown that the principles postulated by Narmer for melodic expectations can be reduced to two basic predictor variables, namely pitch proximity and pitch reversal. The pitch proximity principle states that listeners expect a melodic sequence to continue on a note that is proximate in pitch to the last note. Extending the pitch proximity principle, the pitch reversal principle claims that listeners expect the next note to be close in pitch to the note before the last note. For example, when a melody features a large lead, violating the pitch proximity principle, listeners expect the melody to return to a note close to the note before the lead. According to Narmer, 1990, melodic expectation is governed by innate bottom-up as well as learned top-down processes. This view has been challenged by computational modeling approaches showing that melodic expectation can be accurately modeled based on general learning mechanisms without assuming innate representational rules. Here's 294 Moritzlen and Stefan Kolsch in Wiggins 2012. The learning mechanisms built into the model distinguish between long-term and short-term learning processes. Whereas long-term learning reflects listeners' experiences acquired over previously encountered musical pieces, short-term learning reflects the learning that occurs during exposure of the current piece. Interestingly, the model has begun to be extended to harmony, Worley ETAL 2008, and even language, Wiggins 2011, indicating that it reflects general modality-independent cognitive processes rather than music-specific rules or principles. Although musical expectancies have mostly been investigated in tonal contexts, i.e. in melodies or chord progressions, expectation processes are equally important in the processing of musical rhythm. Studying rhythms of the Black Atlantic diaspora, the rhythms underlying popular music genres such as jazz, blues, reggae, funk, rock, or hip-hop, Pressing, 2002, argues that the emotional effect of these rhythms crucially relies on prediction and expectation processes. Importantly, the expectation processes relevant to mediating musical tension can happen on different cognitive levels and involve different degrees of previously acquired knowledge. They can be knowledge-free, i.e. not relying on long-term knowledge, or they can be based on information stored in long-term memory. For example, expectation generation related to small-scale structures, e.g. the grouping of notes, may depend exclusively on auditory sensory memory and the processing according to Gestalt principles. On the other hand, the formation of expectations can be informed by implicit knowledge of music syntactic structures stored in long-term memory. See Kolsch 2012 for a more detailed discussion of different levels of music processing. It remains to be investigated whether the different levels of cognitive processing involved in the generation of expectancies are associated with tension experiences that are qualitatively different from each other. 14.3.1 Empirical research. Various experimental studies have tapped into the subjective experience of tension. Most research investigating musical tension employs continuous self-report methods, Schubert 2010, to measure the subjective experience of tension. In studies using continuous self-report methods, the tension experience of participants is tracked online during the actual listening experience. In the first empirical study of musical tension, for example, Nielsen, 1983, cited in Krumhansel 1996, used a set of spring-loaded tongs that participants pressed together according to their degree of experienced tension while listening to excerpts from Joseph Haydn's Symphony No. 104 and Richard Strauss' Also Sprach Zarathustra. The deflection of the tongs was recorded and put into relation to different structural features of the music. See below. The tension profiles obtained by Nielsen were replicated by Madsen and Fredrickson, 1993, using the so-called continuous response digital interface, CRDI, a potentiometer that records dial movements of participants while they listen to a piece of music. An alternative method for acquiring tension ratings is to play music to participants until a certain event of interest is reached, then stop the music and ask participants to rate how much tension they experienced or how conclusive the last musical event felt to them, e.g. Bigand ETAL 1996, Bigand and Farncat 1999, Modal and Krumhansel 2007. Other tension resolution patterns. 295 studies use sliders depicted on a screen that can be adjusted with a computer mouse depending on the degree of experienced tension, e.g. Farwood 2012, Krumhansel 1996, Len ETAL 2013. In a web-based survey by Farwood, 2012, tension of short musical excerpts was rated by selecting graphical representations that best corresponded to the excerpt, e.g. an upward rising line symbolizing an increase in tension. Note that when acquiring subjective tension ratings, and emotion ratings in general, one has to distinguish between the tension that is subjectively experienced by participants, felt musical tension, and the tension that participants think that the music expresses, perceived musical tension. This distinction is important because felt and perceived emotion in music do not necessarily coincide. Gabrielson 2002. Musical expectancies have been studied using priming paradigms and the probe tone technique. In priming experiments, participants are presented with a musical event, the prime, that is followed by a target event. When the target is expected, it is processed faster than when it is unexpected. By having participants perform a simple decision task, e.g. deciding whether the target is in or out of tune, response times can be recorded that indicate how expected a specific musical event is in relation to a preceding prime. See, for example, Barucha and Stoacki 1986. In probe tone paradigms, a musical context is played to participants that is followed by a tone, for which participants have to judge how well it fits the preceding musical context. Using this procedure, it is possible to construct a tonal hierarchy that ranks different pitches according to their perceived stability in a given context. See Krumhansel and Shepard 1979, Krumhansel and Kessler 1982. For example, notes of a musical scale are perceived as more or less stable, with the first note of the scale, the tonic, usually being experienced as most stable. Experimental studies also investigated how different musical features influence the subjective experience of tension. The previously mentioned study by Nielsen, 1983, found dynamics, tonal aspects, melodic contour and harmony, timbral features, and repetition to influence ratings of musical tension. Other features that were found to affect tension ratings are phrase structure, note density, Krum-Hansel 1996, pitch height, loudness, onset frequency, and tempo, Farbu 2012. Discarding expressive features of the music, i.e. dynamics and agogics, appears to preserve the overall tension resolution patterns of a musical piece, Krum-Hansel 1996, Len et al. 2013. However, expressive features can enhance the experience of tension, and the contribution of different musical features depends on their relative importance in the specific musical piece, Farbu 2012, Len et al. 2013. Moreover, tension ratings correlate highly within individuals over different exposures, Krum-Hansel 1996, as well as between different groups of persons such as musicians and non-musicians or school children of different ages, Fredrickson 1997, 1999, 2000, suggesting relatively consistent and stable underlying cognitive and affective processes. Tension ratings also have been found to correlate with ratings of discrete emotions, happiness, sadness, and fear, and psychophysiological measures such as finger pulse amplitude, respiration rate, blood pressure, skin conductance, and temperature, Krum-Hansel 1997, thus supporting its role in effective processing. 296 Moritz Len and Stefan Kolsch musical tension has been modeled based on the tonal structure of a musical piece, Lodahl 1996, Lodahl and Krum-Hansel 2007. In these models, tension is estimated by calculating the psychological distance between chords of a musical piece. Chords that are further away from the tonal center of a piece are associated with higher tension values, based on the theory of tonal pitch space, Lodahl 2004, and the hierarchical syntactic structure is described by Lodahl and Jackendorf, 1983. A more recent model of musical tension, Farbu 2012, includes other musical parameters such as loudness, melodic expectation, onset frequency, and pitch height, and also accounts for dynamic cognitive processes, memory and attention, that affect the experience of tension. Altogether, the empirical studies of musical tension indicate that a plethora of features affects the experience of tension, ranging from purely acoustic features such as sensory dissonance or loudness to aspects that require more complex cognitive processing, e.g. the processing of musical syntax. To gain a better understanding of musical tension, future research may profit from a closer investigation of the underlying mechanisms by which different musical features create tension. In particular, it may be useful to investigate to what extent the influence of different features on musical tension can be accounted for by the processes of expectation and prediction discussed above, and to what degree other mechanisms, e.g. sensory dissonance, play a role. 14.3.2 Musical tension and emotion. How do the tension resolution patterns of a musical piece relate to the listener's subjective emotional experience? First, emotional qualities of musical events mediating tension and resolution experiences may partly depend on their specific psychoacoustic properties. For example, musical chords conveying tension often are more dissonant than chords associated with resolution, regardless of the musical context. The experience of dissonance is, at least partly, determined by the sensory processing of sound in the ear. Chords perceived as dissonant often feature frequencies that are close together, causing interferences between the auditory sensory receptors of the basilar membrane in the inner ear, which are perceptually experienced as roughness. Helmholtz 1913. Due to this roughness, chords associated with tension may thus intrinsically be experienced as more unpleasant than consonant chords. 5 Apart from the intrinsic emotional quality of isolated musical events, expectation processes again play a key role in inducing emotional experiences related to tension and resolution during music listening. Previously, we referred to the works by Meyer, 1956, and Huron, 2006, who proposed expectation processes as the driving force behind music-evoked emotions. Likewise, Jesslin and Vasterdahl, 2008, identify musical expectancy as one of 6 mechanisms by which music can induce emotions. The other 5 are brainstem reflexes, evaluative conditioning, emotional contagion, visual imagery, and episodic memory. The power of expectation processes as a mediator of music-evoked emotions is further corroborated by empirical research on so-called chill experiences during music listening. Chills, also referred to as thrills, shivers, or frisson, are intensely pleasurable responses to music that often are associated with specific physical sensations such as shivers. Tension resolution patterns 297 down the spine or goosebumps. For an overview, see Panksepp 1995. Sloboda, 1991, found that these chill experiences often are evoked by new or unexpected harmonies, thus supporting the close connection between expectancy violations and emotional responses. 14.3.3 Underlying brain mechanisms. The advent of modern neuroimaging methods, in particular functional magnetic resonance imaging, fMRI, has opened new avenues for investigating brain processes related to aesthetic experience by providing a non-invasive method for studying cognitive and affective processes in the human brain. Although neuroscientific research that directly investigates the neural correlates of tension resolution patterns is scarce, various studies investigating expectancy violations in music, as well as studies investigating chill experiences, point to brain areas relevant for mediating feelings of tension. Furthermore, there is evidence that the pleasure derived from music listening is driven by neural mechanisms of prediction and expectation associated with dopaminergic neuronal activity in the midbrain. A large body of research has investigated predictive processing in music, reviewed in Rohrmeyer and Kolsch 2012, and neuroscientific studies have begun to identify underlying brain mechanisms. In particular, cognitive processing of expectancy violations in music appears to be associated with specific signatures in the electroencephalogram, EEG. These signatures differ with regard to the level of cognitive processing involved. At a relatively low level of cognitive processing, for example, occasional deviance in a sequence of tones give rise to the so-called mismatch negativity, MMN, a characteristic negativity of event-related scalp potentials, ERPs, peaking around 150-250 ms after the deviating event. For a review, see Nathan et al. 2007. On a higher level of music syntactic processing, expectancy violations in short chord sequences manifest in an early right anterior negativity, ARIN, which peaks around 150-200 ms after an unexpected chord function, Kolsch et al. 2000. In a study using magnetoencephalography, MEG, the neural sources of this brain potential were localized in the inferior frontal gyrus, IFG, Brodmann area 44, Mice et al. 2001. This finding has been corroborated by subsequent fMRI studies, e.g. Kolsch et al. 2005, Tillman et al. 2006, indicating a functional role of the IFG in music syntactic processing. Importantly, however, apart from activating cortical areas involved in syntactic processing, expectancy violations have also been found to activate areas related to emotive processing in the orbitofrontal cortex, Kolsch et al. 2005, Tillman et al. 2006, as well as the amygdala, Kolsch et al. 2008. The amygdala activations in response to irregular musical events are consistent with the observation that expectancy violations in music also evoke autonomic responses such as increases in electrodermal activity, Kolsch et al. 2008b, which are mediated by the central nucleus of the amygdala, Ledoux 2000. A recent fMRI study of our own group, Len et al. 2013, investigated neural correlates of musical tension more directly by relating fMRI data to behavioral tension ratings of 4 piano pieces by Mendelssohn, Mozart, Schubert, and Tchaikovsky. It was found that tension increases, as rated by the participants, were related to signal increases in the orbitofrontal cortex, Brodmann area 47, and the amygdala, consistent with the fMRI studies 298 Moritz Len and Stefan Kolsch mentioned, Kolsch et al. 2005, Tillman et al. 2006, Kolsch et al. 2008. This supports the involvement of orbitofrontal cortex and amygdala in musical tension. There are also hints that certain brain areas are related to the different stages of the tension arc proposed by Kolsch, 2012. Studying neural correlates of chill responses, Salim-Foer and colleagues, 2011, found that anticipation of a chill response and the actual chill response itself were related to different brain areas. Whereas actual chill responses were related to neuronal activity in the ventral striatum, presumably the nucleus accumbens, a structure involved in reward processing, anticipation of chill responses activated more dorsal parts of the striatum. Activations in the same compartment of the dorsal striatum were also evoked by unexpected chords in short chord sequences, Kolsch et al. 2008. Assuming that irregular chords evoke an anticipation for resolution and that the resolution is experienced as pleasurable, it appears that two distinct stages of the aesthetic trajectory, anticipation and resolution, map to specific brain areas in the striatum. However, to disentangle the brain mechanisms underlying the different phases of the aesthetic trajectory, in particular the different stages of the tension arc proposed by Kolsch, 2012, further research is required. In previous sections we mentioned that the predictive processes related to experiences of tension and resolution constitute a fundamental aspect of human cognition and brain functioning. In this regard, the theory of predictive coding, first in 2010, is especially relevant. This theory has been proposed as a unified brain theory, according to which action, perception, and learning can be accounted for by a basic principle, the minimization of prediction errors, i.e. the minimization of surprise. Considering the role of predictive processes in tension resolution phenomena, it seems likely that their appeal and emotional power, at least partly, derive from the fact that they tap into this basic principle of brain functioning. For music, the close relation between the predictive coding theory and music-evoked emotions has been put forward in an article by DeBauer and colleagues, 2012, suggesting that the fulfillment or violation of musical expectancies is associated with activity of the brain's dopaminergic reward system. According to this view, musical expectancies activate dopaminergic neurons in the midbrain, coding information about a listener's expectations concerning upcoming musical events. If these expectations are violated, a prediction error ensues that is associated with emotional experiences. Although the exact neuronal mechanisms by which prediction processes trigger effective responses during music processing remain largely unclear, the theory of predictive coding provides a promising framework from which new insights into the neural mechanisms underlying music-evoked emotions and affective experience in general can be expected in the near future. 14.4 Summary tension resolution patterns are an important artistic device that drives emotional experience in a variety of different art forms, especially in temporal art forms such as music, film, or literature. In this chapter, we discuss general psychological mechanisms underlying tension resolution patterns 299 tension and resolution phenomena. In particular, we argued that experiences of tension build on processes of expectation and anticipation, as well as a general urge to resolve uncertainty, dissonance, and instability and strive towards a stable state of equilibrium. We discussed emotional aspects of tension and resolution phenomena and highlighted their important role in the aesthetic experience of art and their relation to different stages of an aesthetic trajectory. The special case of musical tension was considered in more detail, giving an overview of empirical research that has identified various features mediating experiences of tension and resolution. Finally, we discussed neuroimaging research that has identified limbic and paralimbic structures of the brain related to expectancy violations and chill experiences, and their anticipation, thus pointing to possible neural correlates of tension and resolution experiences. The predictive coding theory was discussed as a promising theoretical framework that may help to integrate aesthetic emotions into a general neurocognitive model of human affect. 15.1 Music and aesthetic emotions in daily life. We are surrounded by music, in the shopping mall, on TV, or on the radio. Nowadays, even while surfing the internet, pop-up commercials might start playing a tune. For the adult layperson, situations where music is listened to intentionally, such as when playing favorite songs on a mobile device or from the hi-fi equipment at home or when attending a concert, happen less frequently compared to instances of casual listening as just described. According to a review by Sloboda, 2010, intentionally listening to music, as the main activity, amounts to only 12% of the total time spent listening to music. Nevertheless, intentional musical activities can be considered as fairly common in daily life, compared to physical activities, for instance, even when a person does not have, or plan to have, a career in music. This is even more common in adolescence, when music assumes a special role in daily life. Saritelio and Hertila 2007. Intentional listening and active musical activities represent typical aesthetic experiences of music, generating effective and evaluative outcomes. Recently, the aesthetic experience of music has been defined as a situation in which an individual approaches a musical event or involves oneself in a musical activity possibly with an aesthetic attitude, intentionality, effective expectations, and dedicated attention. Brattico et al. 2013. Brattico and Pierce 2013. According to the framework developed by Brattico and colleagues, 2013, an aesthetic musical experience in an optimal situation, such as listening to music in a concert hall, would engender three different kinds of aesthetic responses. 1. Aesthetic judgments. This music is so beautiful. 2. Aesthetic emotions, such as when goosebumps appear on the skin or when one bursts into tears while listening to a song. And 3. Preference. I love that song. Although the chronological succession of these responses is yet to be determined, Brattico and her team, 2013, proposed that aesthetic emotions and preference follow aesthetic judgments of beauty or of other formal aspects of the music heard. But can an objective property in music, or even in other art forms, directly engender aesthetic pleasure? How do external stimuli, affective state, and prior listening experience 304 Elvira Brattico coalesce to create idiosyncratic pleasurable responses to music? The paradox of a stimulus which begets a positive aesthetic response despite its intrinsic negative properties exists both in music and in visual arts. Conway and Rinning, 2013, P1, remind us that throughout history, artists have created deeply moving artwork that is emphatically not beautiful. Goya's Saturn devouring one of his sons provides a famous historical example. For instance, a stimulus might originate unpleasant sensations at peripheral organs and hence be associated with withdrawal reactions, and yet simultaneously produce strong feelings of pleasure mediated neurally by higher level mechanisms and psychologically by associations with positive past events or by drives for compliance with clear sets of values. Here, we explore this paradox between sensory pleasure and conscious enjoyment. In some cases the two experiences coincide, in others they are drastically opposite. Several factors modulate the effective and evaluative responses to music, adding to the complexity of the relationship between sensory pleasure and conscious enjoyment. Jesslin and Vastfeld, 2008, identified 6 psychological mechanisms by which music induces emotions identified by brainstem reflexes, evaluative conditioning, emotional contagion, visual imagery, episodic memory, and expectancy, and according to Konechny, 2008, these mechanisms can all be termed extra-musical associations. West and Kring-Gilbach, 2010, listed 2 mechanisms in addition to extra-musical associations, hardwired responses and anticipation, which respectively are reminiscent of the brainstem reflexes and expectancy mechanisms of Jesslin and Vastfeld's proposal. The latter mechanism can be considered the only music-specific one, since it predicts that emotions derive from former knowledge of the temporal course of the music heard, acquired from previous listening. This chapter will analyze the neural mechanisms generating the aesthetic emotion of enjoyment, rather than the psychological ones. First, it will focus on the sensory mechanisms determining the succession of neural events from the periphery to the central nervous system and leading to musical enjoyment. This can be called the sensory hypothesis of musical pleasure. Next, the chapter will introduce the cognitive mechanisms determining musical pleasure that originate from prefrontal and associated cortices and modulate peripheral reactions. This can be considered the conceptual hypothesis of musical pleasure. While reviewing these mechanisms, the paradoxical case of cognitive pleasure or enjoyment that does not match sensory pleasure will be discussed. Finally, the chapter will offer the first formal description of how these two types of neural mechanisms are influenced by internal contextual factors, for example by expertise, mood, personality, and genes, and external contextual factors like the presence of peers in the environment. 15.2 The bottom-up neural route to sensory pleasure. Musical aesthetic experience might lead to conscious judgments of beauty concerning a musical piece or a particular performance. These judgments are often accompanied by hedonic feelings, although not always. A number of psychoacoustic and behavioral studies demonstrated that some perceptual features, like sensory dissonance or consonance, innately trigger pleasant or unpleasant sensations to sounds across cultures and ages, with from pleasure to liking and back 305 empirical evidence obtained even from infants as young as a few months of age. Trainer et al. 2002. Functional magnetic resonance imaging, fMRI, data with infants only a few days old also showed asymmetric activity over the supratemporal plane in the right hemisphere, where the primary auditory cortex is located, while they listened to consonant music as compared with altered dissonant music. Furthermore, altered music, containing out key chords, activated the ventral striatum, which consists of the nucleus accumbens and the ventromedial parts of the caudate and putamen, and in which the neural signal is transmitted mainly by using the neurotransmitter dopamine, and the left amygdala. Perini et al. 2010. These latter findings diverge from what was observed in adults in a pioneering positron emission tomography (PET) study. Blood ETAL 1999 ratings of increasing dissonance were proportionally correlated with neural activity in the right parahippocampal gyrus, not the amygdala, and precuneus, whereas increasing ratings of consonance correlated with activity in the orbitofrontal cortex and subcallosal cingulate. In subsequent neuropsychological studies, patients with lesions in the parahippocampal gyrus, and not a patient with a selective amygdala lesion, exhibited reduced sensitivity to musical unpleasantness with intact emotional recognition of happiness and sadness in consonant music. Gosselin ETAL 2006. Notably, all of these studies reviewed defined dissonance as the alteration of the chord accompaniment of a melody. Although these previous studies seem to rule out a contribution of the amygdala in the perception of musical dissonance, others show that the amygdala does play a role in the perception of negative auditory sensations. For instance, Gosselin and colleagues, 2005, provided evidence that 16 patients with unilateral, left or right, temporal lobe excisions encompassing the amygdala could not perceive fear in music as distinctly as controls could. This impairment in emotional recognition was specific to fear, since the patient's recognition of happy and sad music was normal. For a replication of these findings, see Gosselin ETAL 2011. Furthermore, Kumar and colleagues, 2012, measured the fMRI responses of 16 subjects listening to 74 sounds, including not just musical but also animal and environmental sounds, and rating them according to their pleasantness. Sounds vary greatly in perceived unpleasantness, from very high, e.g. chalk scratching on a blackboard, a knife scraped on a bottle, to very low, e.g. bubbling water. Results revealed the importance of the functional coupling, based on anatomical connections, Ledoux 2012, between the right basolateral nucleus of the amygdala and the left primary auditory cortex for experiencing aversive, unpleasant sensations from sounds. This finding indicates that the amygdala provides the auditory cortex with information about the pleasant or aversive quality of sounds. A recent study by Kolsch and colleagues, 2013, also revealed stronger functional connectivity between the left superficial amygdala and the auditory cortex resulting from higher auditory cortex activity during positive emotions from music, joy compared to fear. Similarly, with intracranial electroencephalography, EEG, recordings on a male patient, Legio Schovel and colleagues, 2014, observed activations of the right amygdala to sad and peaceful emotions induced by 20-second piano pieces and of the left amygdala to only happy pieces. Based on these findings, we can venture to propose that the coupling between the auditory cortex and the amygdala represents a central 306 Elvira Bractico neural mechanism for evoking musical emotions. In contrast, a decoupling between those areas, as observed by Legio Schovel and coworkers, 2014, for angry-sounding music that was strongly disliked by the patient measured might underlie negative aesthetic experiences of music. The lateralized activity of the amygdala according to emotional valence has previously been noticed in a meta-analysis conducted mainly on neuroimaging studies using visual stimuli, Fuser Poly ETAL 2009. However, contrarily to the data obtained with music as stimulus, the left amygdala was activated by negative emotions whereas the right amygdala was activated by positive emotions. Discrepant findings are also present within the literature, and in one meta-analysis focused on the effects of gender, the left amygdala in females was recruited more for negative emotions and in males more for positive emotions. Stevens and Heyman 2012. Based on a few studies with music reviewed here, it seems that the picture for music is more straightforward than for visual stimuli. Nevertheless, the neuroimaging studies on music described above demonstrate the importance of coupling between the amygdala and auditory cortices for the elicitation of an emotional experience from music. While the amygdala, especially in the right hemisphere, and the nearby parahippocampal gyrus might be the necessary relay stations for an aversive, unpleasant sensory experience directly deriving from the acoustic features of the music heard, this striatum, particularly the right nucleus accumbens, see Kolsch 2014, and the caudate nucleus, are the subcortical brain structures important for experiencing very pleasurable sensations from music. To study these subcortical structures, researchers have isolated chills or free zones, which are replicable and measurable bodily responses, associated with shivers down the spine or goosebumps in the skin, triggered by music or other artistic stimuli. Also, climax passages in a speech might trigger chills. Several studies have demonstrated that chills are associated with a strong pleasurable sensation and hence index highly positive emotions induced, for example, by music. Studying the neural correlates of the chill response to familiar, highly pleasurable music, there was evidence that these are associated with activity in reward areas of the brain, such as the ventral striatum, including the nucleus accumbens, and ventral tegmental area, which are regulated by endogenous dopamine transmission. Blood and Data 2001, Herrera ETAL 2011, Menon and Levin in 2005, Salenpo ETAL 2011. Furthermore, in a recent paper it was found that the bodily reactions of chills are anticipated by neural activity in the dorsal striatum, particularly in the right caudate, followed by activation of the ventral striatum, and particularly of the nucleus accumbens, a subcortical nucleus of the mesodopaminergic pathway using mainly dopamine as neurotransmitter. Salenpo ETAL 2011. Additionally, Salenpo and colleagues, 2013, noticed that activity in the dorsal and ventral striatum was concurrent during listening to unfamiliar music, indicating temporal overlap between expectations of the music heard and its positive evaluation, as indexed by the subject's bids mimicking realistic purchasing of a tune on the internet. The apparent discrepancy in the chronological succession of the responses might be explained from pleasure to liking and back 307 by the nature of the expectations to familiar and unfamiliar music, and by the differences in the paradigms. The second study did not measure chill responses. Indeed, the basal ganglia, of which the dorsal striatum is a part, seem to have a role in the online prediction of beat and temporal regularities in music. Grant and Rowe 2013. These studies, though, left open the question of how this pleasurable response originates, be it from bottom-up auditory processing from the periphery to the auditory cortex and then the subcortical nuclei, perhaps even bypassing the auditory cortex, or top-down from higher-order cognitive structures like the prefrontal cortex, posing attitudes and expectations that modulate peripheral responses. 15.3 The top-down neural route to conscious liking. The neural mechanisms described so far rely mainly on subcortical structures and on the auditory cortex. They might operate in a very fast manner and without conscious awareness by the subject. For instance, a very loud and rough sound triggers the acoustic startle reflex by a subcortical nuclei in the brainstem, particularly the caudal pontine reticular nucleus, without fine feature processing by the auditory cortex. Cook 1999. The passage from sensory pleasure to conscious hedonic feeling leading to the liking of a musical piece, or even a sound, involves the mediation of higher-order structures. By using apposite experimental designs, it is possible in the laboratory to isolate the implicit, subconscious neural processes related to an emotional stimulus from those related to its conscious processing. Here we focus on implicit versus explicit tasks that have been used first in visual research. In a recent study, we contrasted individuals who preferred to listen to, and are fans of, the musical genre heavy metal with those individuals who enjoyed listening mainly to the musical genre Latin American music. These preferences might be considered opposites, since fans of one are often critical of the other. In a recent EEG study we took advantage of this feature of musical preferences with a between subjects design in which individuals with clear preferences for heavy metal or Latin American music listened to excerpts of musical tunes belonging to one of those genres. Istoke ETAL 2013. The findings evidence that the late positive event-related brain responses to the music stimuli from the favorite genre were enhanced compared to those to the stimuli from the disliked genre, but only when subjects were performing a descriptive task of classifying the timbre and not when they were consciously deciding whether or not they liked the music. This counterintuitive effect was explained by the authors of the study as due to the phase locking of evoked neural responses, which highlights the preference modulation of auditory processing, locked to the onset of the stimuli, but not the more time-varying evaluative processing associated with conscious liking judgments. In other words, the hedonic responses to favorite music influence perceptual and cognitive processing of music in an implicit way, even when attention is focused on performing a non-effective task. According to some authors, for review, see Hargreaves and North 2010, arousal and valence, or sensory consonance/dissonance, are central components of an aesthetic experience. Here, however, we consider these particularly valence, conceived as sensory 308 Elvira Bractico pleasure as only subcomponents of the musical aesthetic experience. This is similar to how the psychological constructionist account of the brain basis of emotion considers valence and arousal, the two dimensions of core effect, realized by the visceral and peripheral sensory systems and defined as the mental representation of the bodily changes that are sometimes, but not always, experienced as feelings of hedonic pleasure and displeasure with some degree of arousal. Lindquist et al. 2012, p. 125. Core effect is thus viewed as an initial, mainly unconscious stage of affective processing, giving emotional nuance to stimuli and events and largely utilizing subcortical brain structures related to the limbic system. That nuance becomes a conscious emotion, such as sadness, happiness, and conscious enjoyment, only after a conceptual act requiring language, executive attention, episodic memory, and categorization processes, and is controlled mainly by frontal and parietal lobe structures. For instance, the dorsomedial and ventromedial prefrontal cortex, the retrosplenial cortex/posterior cingulate cortex, and the medial temporal lobe are all active when categorizing an emotion or focusing on the emotional content of a stimulus. In the framework proposed by Lindquist and colleagues, these brain structures are hypothesized to store representations of prior experiences to attribute a meaning to a core affective state coming from the self or from others. In turn, the anterior temporal lobe and the ventrolateral prefrontal cortex are involved in conceptualization since they control language functions, which are necessary for categorizing an emotion. The dorsolateral prefrontal cortex, associated with goal-directed control of attention and working memory, is instead recruited for explicitly holding effective information about a stimulus in mind in order to categorize it. In the current proposal, sensory pleasure is viewed as an early affective reaction to music similar to core effect. To become a conscious emotion of enjoyment and engender a liking judgment for a musical piece, sensory pleasure must be followed by value attribution mediated by personal associations, knowledge, social constructs, and other top-down processes, and all controlled by the prefrontal cortex and associative temporoparietal structures of the brain. Salenko and colleagues, 2013, provided the first direct evidence of the interplay between frontal and subcortical structures originating musical pleasure. They revealed that the connectivity between the nucleus accumbens and the auditory cortex represents the core neural mechanism predicting a rewarding response to music, indexed by the high speed given during an auction task. The authors also observed increased connectivity between the nucleus accumbens and the inferior prefrontal cortex, serving to explain the role played by matched or mismatched temporal expectations for harmonic structures in the generation of musical pleasure. An explanatory construct, not much explored within the domain of music emotions, is represented by cognitive dissonance, not to be confused with musical dissonance, which is a very influential theory in social psychology. According to this theory, cognitive dissonance takes place when our actions are in conflict with our prior attitudes and the latter hence change to match the former, avoiding the negative affect resulting from the cognitive conflict. In a study by Van Veen and colleagues, 2009, recruitment of the dorsal anterior cingulate cortex and the anterior insula were found to predict the subsequent changes in attitude by the subjects, in this case, a positive change towards the experimental setting from pleasure to liking and back 309 of the fMRI scanner. Cognitive dissonance might also be a psychological mechanism for pleasure derived from the resolution of mismatching expectations while listening to music. A rare example of a study focusing on the effects of attitudes on auditory processing of the same musical stimuli was conducted by Steinbeis and Kolsch, 2009. In this block design study, participants were convinced that 60 excerpts of musical pieces lasting from 8 to 13 seconds, originally composed by Schoenberg and Webern, were written either by a composer or by a computer while their fMRI signal was measured. When the piece was thought to be the product of a composer, the anterior medial frontal cortex, the superior temporal sulcus, and the temporal poles, namely those brain structures that are typically used when subjects attribute a mental state to another human, were active. Notably, the strength of the activity in the anterior medial frontal cortex even correlated positively with the extent to which the participants thought an intention was being expressed in the musical pieces, as reported in a post-experimental questionnaire. Hence, when an intentional stance is attributed to a musical piece, anterior frontal structures are recruited and assist the listener in interpretation. One could assume that such a search for an intention in the composition is an important stage towards a complete aesthetic experience of music, including a conscious decision of liking. A peculiar case of discrepancy between sensory pleasure and conscious enjoyment occurs when the hedonic response derives from understanding the formal structure of a piece, for example, of contemporary classical music. Think of Sonata No. 1 by Pierre Boulez composed according to the principles of serial music. The affective sensations deriving from the acoustic processing of such a piece might be negative, with strong activity in the parahippocampal gyrus right amygdala, and yet a listener who is able to identify the repetitive notes and to identify the neatness of the construction might still give a positive evaluative judgment of liking and even have hedonic responses with neural activity in the reward system or at least the drive to listen to the same piece again. In the domain of abstract visual art, Letter and colleagues, 2004, named this psychological process cognitive mastering, a crucial stage of the information processing sequence leading to the aesthetic outcomes of judgments and emotions. Perlovsky, 2010a, 2010b, also talks of knowledge instinct as a mechanism generating the aesthetic pleasure which stems from knowledge and understanding. According to this theory, aesthetic emotions are viewed as needs of the mind to understand the ever-changing world by thinking conceptually, whereas basic emotions are considered as bodily instincts. The cognitive consonance or dissonance between the knowledge and the world generates aesthetic emotions of satisfaction or dissatisfaction. Finally, as discussed earlier, cognitive mastering might change the affective state of an individual when facing a musical or other artistic activity. Indeed, familiar music has been shown to activate more limbic subcortical areas than unfamiliar music and even liked music. The positive affect derived from understanding might be related to such a brain response. Overall, in the study by Pereira and colleagues, 2011, subjects like familiar music more than unfamiliar music. In another fMRI study by Chapin and colleagues, 2010, investigating expressivity in music with a real performance of a piano piece and 310 Elvira Bratico digital 1, produced with musical instrument digital interface MIDI, musicians showed higher activity in the ventral striatum than non-musicians while listening to an expressive musical performance. In other words, the study indicated that musicians are better able to master expectations of expressivity and consequently identify the agogic and dynamic variations in a musical performance, which are typically aimed at conveying emotions. This is still an isolated finding, since most previous studies on music expertise have concentrated on cognitive hypotheses rather than on affective ones, but the finding of modulation of limbic and reward activity is expected to be replicated if the hypothesis that cognitive mastering produces positive affect is valid. 15.4 The role of context, social and person-related factors. The aesthetic emotion of musical enjoyment is, however, much more variable across individuals than the mechanistic view of how sensory pleasure arises would predict that neural mechanisms causally link a stimulus with certain acoustic features, e.g. a dissonant sound, to a physiological response, namely the recruitment of parahippocampal gyrus, amygdala, and ventral striatum, and their connectivity with auditory cortex. For instance, in the previous section, it was demonstrated that sensory pleasure might clash with cognitive pleasure, such as when one receives very positive feelings from listening to the very dissonant and loud music of a death metal band. The origins of this paradox might be related to the person or to the social and external context. The physical environment during a musical activity might by itself determine the emotional responses, including enjoyment. For instance, the proximity of a friend while attending a concert, and noticing her facial expressions and bodily reactions while listening to music might trigger mimicry, thanks to the properties of the mirror neuron system, Galiz and Friedberg 2007, and generate similar emotions via the psychological mechanism of emotional contagion. An alternative neural mechanism that has been proposed to underlie emotional contagion is the temporal synchronization of neural activity in the same brain structures between individuals experiencing the same stimulus, such as a movie or musical piece. Namenma et al. 2012. See also Ulrai et al. 2012. The most recent demonstration of the effects of the presence of peers on an aesthetic response to music has been thus far produced by Agerman and colleagues, 2011, using 14 members of an amateur orchestra. By using skin conductance responses, questionnaires, and 10 one-minute classical music excerpts, they reported that both the intensity of emotions prompted by by the music and the frequency of chills experienced, accompanied by a change in skin conductance, were higher when participants listened to the music alone than when in a group. This study did not support the hypothesis of social facilitation by presence of peers, which instead found validation in Lamont's study, 2011, which was not restricted to the classical music genre. In this case, strong experiences of music occurred most typically during a live concert with other listeners present. An important social psychological mechanism affecting musical enjoyment is that of compliance, the desire to comply with what peers do. In a web-based study with more than from pleasure to liking and back 311-5000 participants, Agerman and colleagues, 2013, noticed that online music listeners changed their ratings of arousal more than their ratings of valence for 5 music excerpts of various styles, lasting 30 seconds each, based on social feedback in the form of information from previous music listeners, represented in this experiment by the position of the rating sliders during listening and/or rating. Additionally, the authors included a control condition with a second group of participants where the feedback came directly from the computer predicting the rating responses of the participants. The findings showed that social feedback was again more effective than informational feedback on changing arousal ratings, indicating that the emotional effects of music might be modulated by normative and social drives to conform to the majority. According to the seminal research by Ash, 1955, this type of conformity based on normative influence does not necessarily change one's own attitudes or perception but only the public compliance. According to Agerman and colleagues, 2013, their results diverge from this prediction since they showed changes of felt excitement deriving particularly from social feedback. However, it is not known how long-lasting this effect is nor whether it involves physiological emotional responses as well as changes in the activity of the limbic system. In adolescence, the effects of these social factors, and possibly even others, such as the construction of self-identity through specific behavior, on various kinds of behavior seem to be boosted. In a behavioral study it was found that adolescents took 3 times more risks in a driving game when in the presence of their friends than when performing the game alone. In contrast, peer presence had no influence on risk-taking in the same driving game in adults. Gardner and Steinberg 2005. A follow-up study utilizing fMRI further revealed that adults exhibited higher activity in the lateral prefrontal cortex during the driving game than adolescents, whereas adolescents showed higher activity in the reward structures of the ventral striatum and the orbitofrontal cortex during driving decisions in the presence of their friends than when alone. Chine et al. 2011. Again, interconnectivity between striatofrontal structures might be at the core of the neural mechanism responsible for sensory and conscious musical pleasure and preference. A pioneering study by Burns and colleagues, 2010, asked subjects to rate the liking of songs twice, once just after the first listening and then a second time, with or without popularity ratings shown for each song. Subjects changed their liking ratings by 12% during their second listening and by 22% when popularity ratings were shown. fMRI data showed that activity in the bilateral anterior insula and frontal poles was positively correlated with popularity scores, whereas negative correlations were found in the posterior cingulate cortex. Hence, popularity ratings did not affect conscious enjoyment, called intrinsic preferences by the authors of the study, since no modulation of reward circuits, such as ventral striatum and orbitofrontal cortex, was found. Instead, the drive to match social consensus was associated with a change in internal arousal states, suggesting neural costs and changing prior judgments to conform to those of peers. In other words, the psychological mechanism of cognitive dissonance might have been at play here. In psychology, there is accumulating evidence for a relationship between the aesthetic response of musical preference and person-related factors. For instance, by using 312 Elvira Bratico, a questionnaire survey of about 3,500 individuals, Renfro and Gosling, 2003, noticed that the 4 main types of preferred music were associated with the personality traits of the Big 5 questionnaire: extroversion, agreeableness, conscientiousness, emotional stability and openness, self-views, and cognitive ability. However, more recently these associations of musical preferences with personality traits were proven to be not so robust, whereas a larger proportion of observed variance was explained by gender and age. For instance, older individuals preferred increasingly complex music, females showed higher liking for classical, mainstream, folk, alternative rock, Latino, and music of black origin, MOBO, and men for jazz, dance, rock, and functional music, North 2010. Even the induction of strong musical pleasure can be modulated by internal context. McRae, 2007, found that item 188 of the Neil Personality Inventory, which reads, "Sometimes when I am reading poetry or looking at a work of art, I feel a chill or wave of excitement," was found to be the best indicator of final openness to experience scores in American individuals. Openness is conceived as the breadth, depth, and permeability of consciousness, and in the recurrent need to enlarge and examine experience. McRae and Costa 1997, p. 826. Individuals who score high in openness are curious, innovative, willing to create unusual associations, and also sensitive to art and beauty. Additionally, Grew and colleagues, 2007, found an association between chill experience and reward dependence. Cloninger 1994, a scale related to agreeableness in the Neil Personality Inventory. According to Panksepp, 1995, 2000, and 2010, the reason why individuals who experience more chills are also those with high sensitivity and a tendency towards nurturing and agreeable behavior is to be found in the evolutionary origin of the chill response, which in his opinion must be related to the sensation, and its concurrent strong emotion, of physical separation of the offspring from the mother. In the field of neuroimaging, the relations between personality and brain responses to music, and even more so to music emotions, have been little explored thus far. Montag and colleagues, 2011, were among the first to explore a link between personality traits and brain responses to musical pleasure with fMRI. They asked 33 subjects to bring their favorite and most disliked musical pieces to the lab and then listen to 3 minutes of each song during an fMRI session. As expected from previous studies, favorite music activated the ventral striatum, caudate and nucleus accumbens, as well as the insula and the cuneus. Remarkably, the activity in the nucleus accumbens negatively correlated with self-transcendence, a subscale of the temperament and character inventory, TCI, which explained 25% of its activity. Intelligent absorption scores were also negatively correlated with striatal activity, but did not substantially improve the model when included in the same model as self-transcendence. The growing behavioral evidence supporting the relevance of person-related and social factors in affecting emotional responses to music calls for further neuroimaging investigations to identify the neural underpinnings of these effects. 15.5 The role of genes in idiosyncratic aesthetic emotions in the broader field of affective neuroscience. Variability in emotional responses has often been regarded as random noise or else has substantiated relativistic views of emotion from pleasure to liking and back 313 processing, like the conceptual act model, reducing any emotional experience to an emergent state associated with dynamically varying, and hard to measure, neural networks into a variety of cognitive functions. Lindquist. ETAL 2012. In the music domain, Conathy, 2008, p. 118, pointed out the following methodological problem. The confusion of the music's expressiveness and induced emotion goes further and enters the instructions to the research participants. According to this author, such confusion not only weakens the efficacy of data collection but also leads to the formation of unsubstantiated theories of musical emotions. The picture becomes even more complex when considering the neuroimaging literature, exhibiting discrepancies in the brain structures associated with certain musical emotions, and particularly with sadness and happiness responses to music. Mitterskip-Fowler ETAL 2007, Bratico ETAL 2011, Talfa ETAL 2005. For musical pleasure, the picture seems to be more homogeneous with the ventral striatum, anterior cingulate cortex, and orbitofrontal cortex often recruited. However, the approaches for studying the neural correlates of musical pleasure are varied. Instructions can range from ratings of pleasantness, Kolsch ETAL 2006, to ratings of likability, Montag ETAL 2011, or brain responses could be selected based on coinciding bodily changes, Salenpo ETAL 2011, leading to some inconsistency in the conclusions that can be drawn from these studies. For instance, chills can be used as markers for high musical pleasure, Brew ETAL 2009, but they occur in the minority of the population and involve substantial bodily reactions whose neural generators have not yet been directly identified. However, taking into consideration that music-related emotions, like enjoyment, are highly variable and subjective, this idiosyncrasy cannot be ascribed only to the extra-musical associations and the mutable, hard-to-predict, life circumstances determining the internal and external contexts of a musical experience, nor to the discrepancies between stimulation paradigms and experimental procedures. Low-level sensory processes already vary between individuals and within the same individual in quite a stable way due to inborn, genetic predispositions for micro and macrostructural physiological properties of critical brain regions such as the auditory cortex and amygdala, which are both crucial for musical emotions. The novel avenue of imaging genetics permits the tracing of variability in emotions and their neural correlates to an individual's biology, to gender, personality traits, and genetic variants. Munoz et al. 2009. For instance, the functionality of the amygdala has been linked to genetic polymorphisms, for example, in serotonin-related, Carrere et al. 2002, or in dopamine-related genes, Blazy et al. 2009, as well as correlated to personality traits such as emotional stability or openness to experience, Pacina et al. 2013. In a study by Blazy and colleagues, 2009, the functional DRD2RS10765660 polymorphism was associated with greater amygdala activity during the implicit processing of facial expressions and greater dorsolateral prefrontal cortex activity during explicit emotional processing. In addition, Carrere and colleagues, 2002, discovered that individual variability in the processing of fearful stimuli was associated with a functional polymorphism of the serotonin transporter, 5-HTT, gene and with amygdala reactivity, a finding at least partially replicated in recent meta-analyses, Murphy et al. 2013. Consequently, the individual variations in mesolimbic and corticostriatocortical circuits during emotion 314 Elvira-Bratico processing might not merely be the result of measurement noise, experimental protocols, or contextual factors, but might systematically result from dopaminergic or serotonergic genes, for example. Those predispositions might in turn explain part of the behavior involving experiencing strong pleasurable emotions derived from music. Furthermore, the human population contains a small percentage of people with a peculiar inborn inheritable disorder specific to music, named tone deafness, implying, for instance, the inability to recognize even famous tunes, or congenital amnesia, Parrots et al. 2002, 2005, 2009, accompanied by normal cognitive functioning and other auditory and speech abilities. This disorder, originating from dysfunctional connectivity between the auditory cortex and the inferior prefrontal cortex, hints at the genetic foundations of brain-based music functions. Recent genetic studies involving twins and families indeed revealed that there exist predispositions for musical abilities enabling some individuals to be more or less hardwired for musical activities than others. Akala et al. 2009, Akalabodi et al. 2011, 2013, for review, see Levin in 2012. Such candidate genes with variations associated with superior musical skills were the arginine vasopressin receptor gene AVPR1A, associated with scores in an audio structuring test and listening behavior, as well as its epistatus, interaction, with the human serotonin transporter gene SLC6A4, UNC5C, adenylate cyclase A, connected to synaptic plasticity and highly expressed in the central nervous system gene UGTA, Akalabodi et al. 2013, Park et al. 2012. With a complex behavioral trait like musicality, more than one gene is possibly in play. Music is likely to be the result of thousands of small effect loci, which together can produce significant heritability quotients, P636, as Levin recently proposed, Levin in 2012. However, even if musicality skills have been correlated with the morphology and functionality of Heschel-Starus, Schneider et al. 2002, thus far no study has directly tested any links between the auditory system or limbic system functions and genotypes previously associated with musicality skills. Such links are of particular interest here because they would establish whether genes predispose an individual for musicality merely through boosting perceptual skills via the enhancement of neural discrimination abilities in the primary auditory cortex and or via increasing the functional connectivity between the auditory cortex and the subcortical emotion-related structures, such as the amygdala, nucleus accumbens, and the basal ganglia, as studies on musical emotion seem to indicate. 15.6 Conclusion. This chapter reviewed brain-based evidence supporting two hypotheses previously tested only within the domain of visual arts, e.g. Kupchak et al. 2009, Thockrell et al. 2012. First, the sensory hypothesis founding a pleasurable experience of music in bottom-up mechanisms, and second, the conceptual hypothesis centering the aesthetic enjoyment of music on prefrontal structures and the internal and social factors modulating them. To borrow Thockrell and colleagues' words, 2012, this aesthetic experience of beauty has been hypothesized to intimately depend on visual sensory details in the art, such as the wavy lines and colors that constitute the modern painting stairway at Auvers by Van Gogh. It has also been hypothesized that aesthetic experience depends on concepts or thoughts associated with viewing art to a greater degree than visual sensory details, such as the contemporary sculpture Brillo soap pads box by Andy Warhol that is nearly identical perceptually to those that were once found on supermarket shelves. In the current chapter, the cognitive roots in the brain leading to the conscious enjoyment of music have been illustrated from the perspective of both internal and social factors. These factors can sometimes be so powerful as to detach the sensory response coming from the inner ear and reaching the brainstem and the amygdala/parahippocampal gyrus, e.g. loudness or sensory dissonance, from the conscious enjoyment mediated by internal and social determinants, and accompanied by the tendency to an approach action exemplified by the drive to listen repeatedly to the same musical piece in spite of the aversive, almost painful, sensations it induces. Rock music concerts, often loud enough to cause tinnitus in the attendees, e.g. Bogish et al. 2005, provide an example of stimulating this behavior. Future research should pay more attention to the underlying social and internal mechanisms generating emotional reactions to music and to how they change our brain processing of it. 16.1 Introduction. There is relatively little empirical research that specifically addresses the question of expertise effects on musical appreciation, but an anecdote will serve to make the importance of the issue clear. Recently, I attended a concert with a friend and, afterwards, discussing the performance, mentioned that I had found the timing a little erratic. My companion replied, "Well, I'm no expert but I enjoyed the concert. Is musical training or expertise important for the appreciation of music? Or can anyone appreciate music? Does it depend on the type of music? If training is important, which aspects are crucial? Which components of aesthetic experience do those aspects of training affect?" These questions have deep implications for the importance of musical training and experience in education and development of artistic appreciation. The goal of this chapter is to establish a framework for generating and testing hypotheses about the effects of musical expertise on the appreciation of music. Before we embark, it's worth pausing to consider a few important methodological points. See Schellenberg 2006. The vast majority of psychological and neuroscientific research on the effects of musical training has taken a cross-sectional approach by comparing musicians and non-musicians on some particular measure. However, this does not demonstrate a causal effect of musical training, since it cannot be known whether the measure in question differed between the groups before commencement of musical training. It may even have influenced the initiation and maintenance of musical training leading to expertise. Second, it is difficult to know how specific the effect is to musical training per SE unless a control group of experts in another domain are also studied, e.g. Dick et al. 2011, Schellenberg 2004, which is rare in the literature. Third, there are many demographic factors, e.g. socioeconomic status, that correlate with musical education, so it is difficult to isolate any effects of musical training unless control groups matched for these factors are included. Usually they are not. With those caveats in mind, we begin our inquiry by locating music and musical expertise in more precise terms. 320 Marcus T. Pierce 16.2 What is music? Music is a complex phenomenon that belies definition, leading Edgar Varese to describe his own compositions very generally as organized sound. Varese and Lynch on 1966. Virtually omnipresent across cultures, music consists of patterns of human-initiated sound extended in time, sometimes associated with visual displays, and used in a bewildering variety of contexts for an enormous range of purposes. We might have more success if we follow a cognitive scientific approach and attempt to pin down the ways in which a musical object may be instantiated in different kinds of representation. Music can be represented in at least three ways. See Babbitt 1965. 1. Physically, as an acoustic phenomenon, traditionally resulting from human movement. 2. In symbolic encodings usually designed for recording compositions and giving directions for their performance, e.g. scores, vocal representations, piano roll representations and sequencers and other software. 3. In various kinds of cognitive and neural representation, e.g. procedural memory, perceptual, and cognitive representations. Representations of music may vary across multiple dimensions: pitch, timbre, timing, duration, loudness, spatial location, and other more complex characteristics relating to harmonic movement, metrical structure, and overall form. In trying to identify objective properties of musical sounds, one quickly finds oneself moving from the acoustic domain, represented by the first category above, into the psychological domain, represented by the third category. 0.2 meter, for example, has no well-defined interpretation as an objective property of sounds, without a cognitive model to interpret metrical structure from those sounds. Nonetheless, this characterization of music is useful for our present purposes since it allows us to identify different kinds of expertise afforded by the phenomenon of music. A given individual might not have expertise in all three domains. A piano tuner, for example, is an expert primarily in the acoustic domain, while a medieval scribe would have been an expert in the symbolic domain of music notation. However, it is difficult to distinguish music from non-music unless one considers the psychological domain, which is the proper place to start investigating musical appreciation. In fact, both the piano tuner and the scribe, as listeners, also have a psychological experience of sound and surely draw on that experience in applying their different trades. Later, we will be interested in the relationship between sound as an acoustic phenomenon and music as a psychological phenomenon experienced by a listener. As a psychological phenomenon, music involves a communicative process in which an audience receives, cognitively/neurally represents, and processes sensory input, whether from acoustic or visual input or both, and appreciates it as music. We might argue that organized sound only becomes music when it is psychologically represented as such by a listener. Musical communication typically involves a composer, a performer, and a listener. Kendall and Carter at 1990, who may be different individuals or groups depending on the effects of expertise on processes involved in musical appreciation. 321 situation, e.g. in improvisation the distinction between the composer and performer is blurred. The performer can be his or her own audience. Individuals may develop expertise in any or all of these areas. One may be an expert in composition, improvisation, conducting, performance, listening, e.g. as a critic, analyst, theorist, producer, DJ, among other things. Within each of these areas, expertise may relate to different compositional tools, instruments, musical genres, symbolic encodings, and so on. 16.3 Frameworks for understanding expertise of music itself is a slippery concept to define, then musical expertise is even more so. A long tradition of research in cognitive science and artificial intelligence focuses on the study of experts in various domains, e.g. board games, science, medicine, the arts, sport, Erickson 2006. This research has tended to characterize expertise as unusually high performance and specialized skills, acquired over many years of focused training and deliberate practice. Feltavish, Pritula, and Erickson, 2006, identify the following generalizable characteristics of expertise. 1. Limited in scope and non-transferable. 2. Comprises a large amount of knowledge. 3. Features larger and more integrated cognitive units. 4. Exhibits functional, abstracted representations of presented information. 5. Automation of basic strokes or movements. 6. Shows selective access to relevant information. 7. Includes an ability to reflect consciously on the expert domain. 8. Comprises efficient and effective adaptation to the task. 9. Requires more than simple experience for its development. Many of these can be found in musical experts. Lehman and Gruber 2006. One prediction that can be made is that the effects of musical expertise should be limited in scope and non-transferable to other domains, and items 5-9 are likely to be characteristic of expertise in music performance. However, items 3 and 4 are especially relevant to perception and appreciation, since they concern cognitive representations rather than the generation of expert performance. On this basis, we might hypothesize that musical experts represent music to themselves. 1. In larger chunks or longer-lasting excerpts, both in short-term memory, but also to facilitate efficient retrieval from long-term memory. 2. As deep, abstract, generalized structures, suited to functional transfer across musical situations, rather than surface characteristics of the music. These hypotheses are partially congruent with research on perceptual expertise, either pre-existing or trained, primarily using visual discrimination paradigms. UKE TAL 2006. First, experts show holistic processing of visual images. For example, the 322 Marcus T. Pearson version effect describes the observation that experts show impaired recognition of vertical inversions of objects taken from the expert domain. Roshan and Kern 2010. Second, experts have stronger relational processing in which spatial relations between the component parts are encoded to a greater extent than non-experts. Gautier and Tar 2002, Gautier ETAL 1998. These imply global kind of configural processing, which is compatible with larger chunk sizes of information and abstract representations. However, this research also finds evidence for more detailed representation of the stimulus. For example, the entry-level shift, where expertise leads to faster discrimination responses to differences at specific levels of detail and more general levels of detail. According to the expertise hypothesis, general-purpose brain regions become specialized for objects of expertise indexed by neural responses such as the N170, Pol 1994, and blood oxygen level dependent, BOLD, responses in the inferior temporal cortex, Gautier ETAL 2000. It is worth noting that there is considerable controversy about this hypothesis, Robbins and McCone 2007. Can these approaches be generalized to musical expertise? If so, we might look for the following attributes in musicians. 1. Musical representations present in larger chunks than in non-experts. 2. Abstract, generalized representations, holistic processing. 3. Greater sensitivity to relations between musical structures. 4. Greater sensitivity to more specific levels of detail in musical structure. The last item might seem paradoxical in combination with the first three items. However, if we allow for multiple levels of cognitive representation, Marr 1982, McClellan 1991, there is no reason why expertise should not lead to both more abstract and more detailed representations. We return to these hypothesized effects below. 16.4 Musical expertise. It is important to distinguish musical training from musical expertise, since one can exist without the other. Musical training, like any form of training, does not always lead to expertise. Less obviously, expertise can sometimes be attained without explicit, formal training. Sloboda 1991. Musical training might refer to a number of different things depending on the kind of expertise targeted and reflecting the fact that, as we have seen, musical practice involves a diverse range of skills, each of which might be emphasized to different degrees in any one program of training. However, in contemporary Western cultures, the primary goal of musical training is usually to attain a high level of performance in playing a musical instrument, which may be the voice itself. In some cases, this is combined with training in other art forms such as dance, theater, and so on. Because training is easier to quantify than expertise, in much of the research performed to date, questions about the effects of expertise in musicianship are often reduced to questions about the effects of musical training. Furthermore, training is often quantified in terms of number of years of formal lessons, but this may not be a good proxy for the extent of actual effects of expertise on processes involved in musical appreciation. 323 Practice. Even when hours of practice are assessed, the effects of practice on expertise may vary depending on the individual concerned and the nature of the practice. It is remarkable how much implicit understanding of music can be acquired merely through exposure without the need for explicit musical training. Indeed, research has shown non-musicians to possess sophistication in such a wide range of abilities related to musical perception that they have been characterized as musically experienced listeners. Bigand and Kulincharna 2006. Sloboda, 1991, goes further, characterizing musical expertise itself as an emotional sensitivity to the music of a given culture possessed by many, or perhaps, most, individuals within a culture. According to Sloboda, this sensitivity depends on 1. The existence in a culture of forms that have perceptible structures of certain kinds. 2. Frequent and formal exposure to examples of these forms over a lifetime. 3. The existence of a normal range of human emotional responses. 4. The opportunity to experience those emotions mediated through perceived musical structures, which itself requires. 5. The opportunity to experience music in contexts free of externally imposed constraints or negative reinforcements. We might start our inquiry, therefore, by investigating whether musical training has any effect at all on the different components of this conception of musical expertise as emotional sensitivity. Taking a slightly broader perspective than Sloboda, 1991, and combining the related points 4 and 5 above, this entails asking the following 4 questions. 1. Are there effects of musical training on the perception and cognition of musical structure, separable from mere exposure? 2. Are there effects of musical training on the frequency of informal exposure to music? 3. Are there effects of musical training on the experience of human emotion? 4. Are there effects of musical training on the emotional and aesthetic experience of music? These questions will be addressed in the following sections. 16.5 Expertise effects on perception and cognition of musical structure. The most striking features of musical expertise are the perceptual motor skills necessary to physically perform highly complex sequences of actions on a musical instrument. For example, in highly trained musicians, we observe changes in neural organization in the anatomical regions of motor cortex responsible for controlling the relevant effectors, e.g. the left hand for violinists, Amunds et al. 1997, Bangert and Schlag 2006. Furthermore, there is some evidence that a sensitive period exists, prior to the age of 7, during which musical training has particularly marked effects on behavioral and neural markers of auditory and motor development, Penhun 2011. 324 Marcus T. Pierce. What about perceptual skills? Based on the literature on expertise, we might predict that musical training would lead to more abstract representation of music, with larger chunks of musical material held in memory and greater integration between the component parts. To address this question, researchers have studied the aesthetic judgment of musicians and non-musicians for pieces of music in which the large-scale tonal form has been disrupted by rearranging or rewriting certain parts. The results consistently suggest that musicians are no more affected than non-musicians by these disruptions. Cook 1987, Carno and Konechny 1992, Marvin and Brinkman 1999, suggesting that both rely more on local representation than on high-level, integrated representations of large-scale tonal closure. At the other end of the scale, it seems likely that extensive periods of time spent in focused listening to music would sharpen auditory perception. There is evidence suggesting that this is the case. Professional musicians show smaller pitch discrimination thresholds for pure and complex tones than non-musicians. Michel et al. 2006. These effects may increase with number of years of musical training. Kishan Rabin et al. 2001, and there is some evidence that pitch discrimination is better in musicians who habitually tune their instruments. Michel et al. 2006. Musicians are also better than non-musicians at discriminating temporal intervals. Benai et al. 2012, as well as a range of other auditory temporal tasks. Ramsayer and Altenmuller 2006. These effects suggest that musical training has a positive influence on the efficiency with which sounds are encoded. Musicians show optimized perception and discrimination of pitch and timbre, in some cases related specifically to their particular instrument. How do these effects of musical training on low-level auditory processing influence the higher-level cognitive processing of music? In processing rhythm and meter, for example, there is evidence that musicians represent deeper metrical hierarchies than non-musicians. Palmer and Krumhansel 1990. Musicians are sensitive to a greater range of features, e.g. slurs, breaths, articulation, and timbre, in identifying grouping boundaries in music. Doge 1987. This presumably allows musicians to make finer-grained distinctions in their interpretations of metrical and grouping structure, facilitating temporal prediction of events. More predictable music in turn is better remembered. Ackers et al. 2013, Schmuckler 1997, and evidence suggests that musicians show better recognition memory for melodies than non-musicians. Dowling and Bartlett 1981, Dowling 1978, Forsmont and Miller 1999, perhaps because they have more accurate predictive models. Research directly examining predictive processing of music is relevant here. General theories of sensory processing in cognitive science and cognitive neuroscience include top-down prediction as a central component in constructing coherent representations of incoming sensory input. Barlow 1959, Dine et al. 1995, Friston 2005, Gregory 1980, Helmholtz 1866. Recent incarnations of this approach take a probabilistic approach in a hierarchical framework where information is processed over successively larger time windows at higher scales in the hierarchy. Friston 2005, Friston and Keeble 2009. According to this theory of perception, learning is driven by prediction errors, occurring when bottom-up sensory input conflicts with top-down prediction. Therefore, violations of expectation are of central importance in understanding how the brain constructs optimized effects of expertise on processes involved in musical appreciation. 325 models of sensory input through experience. If musical training optimizes those top-down predictive models, then we should observe differences between experts and non-experts in terms of prediction error. Recent research suggests that expectations in music are acquired through a process of statistical learning in which listeners construct implicit probabilistic models of the next element in a musical sequence given the preceding context both at the psychological. Huron 2006, Meyer 1957, Foreman and Cuddy 1995, Pearson Wiggins 2006, Tillman et al. 2000, and neural levels, Kim et al. 2011, Lowey et al. 2009, Pierce et al. 2010. The majority of behavioral research on expectation and music perception has found that the expectations of non-musicians look very similar to those of musicians. Bigand et al. 2003, Schellenberg 1996, although some research has identified differences. Pierce et al. 2010. However, neuroscientific studies on musical expectations, using electroencephalography, EEG, and magnetoencephalography, MEG, have revealed differences in neural responses of experts and non-experts to violations of musical expectation, i.e. prediction errors. Research introducing low-probability auditory events and simple melodic tone sequences has found larger event-related potentials, ERPs, in auditory cortical regions for musicians compared to non-musicians. In a MEG study, for example, Fujoka, Trainer, Ross, Keikaji, and Pantev, 2004, examined neural responses to notes forming deviant contours or intervals in short 5-note melodies, finding that the mismatch negativity, MMN, response was significantly larger in musicians than non-musicians for both interval and contour deviance, while no difference was observed for a pitch deviant control condition. There is also evidence that instrument-specific musical training affects sensitivity to timbre. Pantev, Roberts, Schultz, Engelin, and Ross, 2001, presented trumpeters and violinists with oddball sequences reproduced on the trumpet or the violin during EEG recording. The results indicated a larger N1 response to the oddball presented in the timbre of their own instrument. In addition to instrument-specific differences in neural processing of prediction errors, additional research has shown style-specific differences between jazz, classical, or pop musicians processing deviance in terms of pitch missending, intensity, timbre, sound source location, rhythm, and pitch slide. Blust ETAL 2012. Effects of musical training are also observed for violations of temporal expectations. In a MEG study, jazz musicians showed a left lateralized MMN to violations of metrical expectation, while in non-musicians the response was right lateralized. Blust ETAL 2005. Using elegantly manipulated drum patterns, Gazer, Sandman, Jank, and Meyer, 2010, examined the MMN to meter congruent and meter incongruent deviance. Trained percussionists showed a greater difference in MMN amplitude between these conditions than non-musicians, suggesting a greater sensitivity to violations of metrical structure. Related effects of musical training have been found in neural processing of harmonic movement. Stylistically unexpected chords generate characteristic neural responses, including an early right anterior negativity, ARIN, peaking at around 180 milliseconds post-stimulus, Kolsch ETAL 2000. Furthermore, the ARIN has been observed both in artificial grammars, Lowy ETAL 2009, and in real musical examples, Kolsch ETAL 2008, Steinbeis ETAL 326, Marcus T. Pierce 2006. Although the ARIN is present in non-musicians, it has a greater amplitude in trained musicians, Kolsch ETAL 2002. It seems, then, that musicians show larger neural prediction errors to violations of musical syntax. One plausible explanation is that musical training produces more specific, and more accurate, expectations for forthcoming musical structures, resulting from an optimized predictive model. Recent research has examined this question using a probabilistic cognitive model of auditory expectation which acquires pitch expectations through statistical learning of sequential dependencies in music, Pierce 2005. The trained model generates a probability distribution, whose entropy reflects how uncertain the model is about the continuation of the current context, and whose components reflect the likelihood of each possible continuation, given the preceding context, in terms of information content, K 2003. Using this model to select melodic contexts that differ systematically in entropy, Hansen and Pierce, 2014, found that musicians showed lower levels of uncertainty overall but also were better able to distinguish high and low entropy contexts than non-musicians. In particular, the musicians were able to make better use of the predictive cues in low entropy contexts to generate more accurate expectations and showed greater prediction errors to low probability continuations in those contexts. Furthermore, the degree to which listeners' expectations match those of the probabilistic model increased linearly with extent of musical training. These results suggest that musical training can lead to optimized predictive models of musical structure. However, the question arises of whether the crucial factor is musical training per SE, or style-specific training and experience. In a follow-up study, Hansen et al. 2013, examined predictive uncertainty for contexts taken from solos by Charlie Parker in professional jazz and classical musicians as well as non-musicians. The results suggest that the predictive advantage in low entropy contexts, shown by greater prediction errors to low probability continuations, is greater for jazz musicians than classical musicians, although both groups outperform non-musicians. While style-specific training and experience appears to be important, the question of whether these effects are driven by experience or training remains unanswered. 16.6 Expertise effects on frequency of exposure to music is in other domains. Expertise in music requires enormous amounts of time spent in deliberate practice. In fact, hours of deliberate practice is a significant predictor of level of expertise attained. Sloboda et al. 1996. However, it is highly likely that musicians listen to more music throughout their lives than non-musicians, through individual practice, group practice, critical listening to music, concert attendance, and other activities. Perhaps more importantly, they experience music in more focused and, crucially, more emotionally charged situations than non-musicians. Might this more focused and emotionally engaged exposure, rather than explicit training per SE, have any effect on musical appreciation? We know that exposure to music, as with other sensory stimuli, has a strong influence on its perception and appreciation. For example, passive exposure to music appears to be effects of expertise on processes involved in musical appreciation 327 fundamental in the development of metrical perception, Hannon and Trehub 2005, Hannon et al. 2012, and increasing exposure to familiarity with a stimulus, e.g. a musical style, increases subjective preference for it, Ornstein and D'Agostino 1992. The effect of mere exposure on aesthetic experience may, according to one theory, Huron 2006, River et al. 1998, be directly related to the predictive processing discussed in the previous section if pleasure results from the perceptual fluency, facilitated processing and reduced cognitive load, associated with more accurate predictive models, acquired through exposure and familiarity. As noted earlier, there is a thorny methodological problem in distinguishing the effects of explicit musical training from the effects of increased exposure, since musicians are likely to spend more time listening to music than non-musicians. Furthermore, musicians are more likely to engage in focused listening to music, and we know that the efficiency of statistical learning is affected by attentional mechanisms, Toro et al. 2005. At this stage, therefore, it is at least plausible that the greater amount of time musicians spend in focused listening to music, in combination with the effects of musical training per SE, leads to more accurate predictive models which, in turn, may impact on aesthetic experience through increased perceptual fluency. We return to this point later. 16.7 Expertise effects on emotional experience. Our third question is whether musical training affects the general experience of emotion. In a study of school children, Schellenberg, 2004, found that 36 weeks of weekly music lessons increased ability in full-scale IQ and its index scores, verbal comprehension, perceptual organization, freedom from distractibility, processing speed, more than did taking equivalent lessons in drama. However, subsequent studies have shown that musical training does not affect emotional intelligence in adults, Schellenberg 2011, or emotion comprehension in children, Schellenberg and Mancarius 2012. There is evidence that musicians and 7-year-old children randomly assigned to 1 year of musical training show better emotion recognition for speech prosody, Thompson et al. 2004, and that this persists even when groups are matched for cognitive ability, Lima and Castro 2011. However, it is important to distinguish between the experience of emotion and the perception or recognition of emotion in a stimulus such as language or music, Jesslin and Baspal 2008. These findings do not necessarily indicate a difference in the experience of emotion itself, only a better ability to recognize emotion in speech prosody. Therefore, there is no evidence to suggest that musicians differ from non-musicians in terms of their experience of emotion as a result of their musical training, although this does have other effects on general cognitive abilities. 16.8 Expertise effects on emotional and aesthetic experience of music. If emotional experiences of music depend on understanding of high-level musical structure, then we would expect any effects of musical training on musical perception and 328 Marcus T. Pierce cognition to have concomitant effects on the emotional experience of music. Again, it is important here to distinguish the recognition of emotion in music from the induction of emotion by music, Jesslin and Baspal 2008. Regarding the effects of musical training, the majority of research has addressed emotion recognition in Western instrumental music. In general, the evidence suggests that musical training has very little effect on the perception of emotion in music in adults. Bigham et al. 2005, Edmondson 1966, Hefner 1935, Robaza et al. 1994, Waterman 1996, for children, Robaza et al. 1994, Derwalk and Van Grimpen 1991. Even the training-related differences in the perception of emotion in speech prosody discussed earlier are weaker or absent when tone sequences mimicking speech prosody are used. Thompson et al. 2004, Trimmer and Cuddy 2008. There is, however, evidence to suggest that musicians may make less use of emotion in making aesthetic judgments of music. In an ERP study of responses to chord sequences in which the final chord varied in terms of its harmonic congruency with the context, Muller, Hofel, Brattico, and Jacobson, 2010, found enhanced emotion-related neural processing, delayed positive potential, LPP, at KETAL 2006, for beauty judgments compared with judgments about how correct each chord sequence sounded in non-musicians but not in musicians. It is possible that musicians make less use of emotion and rely on other factors in making aesthetic judgments of music. What might these factors be? Scientific theories of aesthetic experience emphasize a number of different cognitive components involved. Brattico and Pierce 2013, letter ETAL 2004, letter 2013, in addition to emotional experience. These range from basic perceptual processing, through effects of attention, memory, knowledge, and judgment. Perhaps the most studied of these are aesthetic judgments for liking, pleasantness, or preference. Here we examine two potential factors affecting aesthetic judgment, musical complexity and dissonance. 16.8.1 Complexity. Wilhelm Wundt, a founder of experimental psychology and one-time assistant of Hermann Helmholtz in Heidelberg, demonstrated that physiological arousal is related to stimulus complexity and argued that aesthetic pleasure is maximal at intermediate degrees of complexity. Wundt 1874. In his New Experimental Aesthetics, Berlin, 1974, developed this idea further, positing an inverted U-shaped function, sometimes called the Wundt curve, linking the arousal potential of a stimulus with its hedonic value. Berlin's research attempted to identify how stimulus properties, such as complexity, familiarity, novelty, uncertainty, influence aspects of the aesthetic experience such as arousal, pleasure, and level of interest. Support for a U-shaped relationship between complexity and liking has been found in artificial auditory stimuli, Crozier 1974, Hayduke 1975, Fitz 1966, and in musical styles ranging from Baroque, Romantic, and Serial, Burke and Gridley 1990, Jazz, Gordon and Gridley 2013, Bluegrass, Orr and Olson 2001, and Pop, North and Hargreaves 1995. If musical expertise facilitates more sophisticated cognitive representations of music, then effects of expertise on processes involved in musical appreciation 329 we would predict that musical training would shift the U-shaped function towards optimal preference for greater degrees of objective stimulus complexity. Importantly, this prediction hinges on an objective definition of complexity. With changes of expertise or familiarity, we would expect the relationship between objective and subjective complexity to change, while the relationship between subjective complexity and liking remains constant, with moderate degrees of subjective complexity producing optimal liking. See Orr and Olson 2005. There is some evidence that this effect of expertise on the relationship between objective complexity and aesthetic experience does, in fact, hold. Ruth and Rapson, 1940, reported a positive correlation between degree of musical training and liking for modern music. In an investigation of preferences for world music, Funk, 1996, found that musicians preferred excerpts with very complex texture, whereas non-musicians preferred moderately complex textures. Burke and Gridley, 1990, showed that musically trained individuals exhibit greater relative preference for complex musical works, by Debussy and Boulez, over less complex compositions, by Bach, Grieg, than non-musicians. In a verbal association task, Isto and colleagues, 2009, found that musicians use more adjectives related to originality and variety, and fewer terms related to mood or mood induction, than non-musicians, to describe the aesthetic value of music. These results are somewhat difficult to interpret since the verbal responses may reflect cultural or professional norms related to expertise rather than psychological experience per SE. Other research has empirically tested the effects of expertise on the inverted U-shaped relationship in music more directly. North and Hargreaves, 1995, for example, examined excerpts of popular music, finding that the inverted U relationship between liking and subjective complexity peaked at a slightly lower complexity level for non-musicians than for individuals with intermediate or high levels of musical training. The relationship between complexity, preference, and expertise may even reflect more specific effects of stylistic musical training. Using a paradigm developed in research on music education, Kagawa, 2004, examined preferences for 4 jazz tunes varying in complexity, as defined by the experimenter, by jazz musicians studying at university. The ratings of the two groups differed only for the most complex music, for which the jazz musicians reported stronger aesthetic experience than non-jazz musicians. Other results apparently contradict this overall picture. Using specially composed jazz and bluegrass improvisations, Orr and Olson, 2001, found an inverted U-shaped relationship between subjective complexity and liking in non-musicians for bluegrass but weaker support for the jazz excerpts. In a subsequent study, Orr and Olson, 2005, asked professional jazz and bluegrass musicians to rate their liking for short jazz and bluegrass compositions. Comparing the responses of the musicians with non-musicians from an earlier study, Orr and Olson 2001, the results suggested that musical training dissolves the U-shaped relationship between complexity and liking. This may be because experts focus on different aspects of musical structure, such as harmony, Conley 1981, when making complexity judgments. It is also likely that other factors besides complexity, such 330 Marcus T. Pierce's expressive performance, Clark 1993, Rep 1992, play a greater role in experts' aesthetic experience of music. Running through this work is the problem of obtaining a broad enough range of objective complexity to observe the complete inverted U-shaped function. In most of these studies, complexity is defined subjectively, either by the experimenter or by the participants in the studies. Therefore, we lack insight into which aspects of musical structure contribute to the perception of complexity and, therefore, liking. One way of avoiding this problem is to bypass the complexities of real music and isolate the structures of interest with objective measures of complexity. A successful approach has been to create stimuli that systematically vary in information content, an objective information theoretic measure of complexity. Research on the pleasantness of artificial tone sequences, Crozier 1974, Fitz 1966, and piano themes, Simon and Walwell 1968, suggests that individuals with musical training show greater preferences for more complex stimuli than non-musicians. Smith and Laura, 1990, assessed aesthetic responses to harmonic progressions, sequences of chords, varying in degree of syntactic prototypicality to test the hypothesis that unpredictable musical events are experienced as pleasant. The results indicated that all subjects, even novices, found atypical progressions more interesting/complex, but non-musicians and undergraduate musicians preferred harmonic prototypes, while only music graduate students preferred atypical progressions. 16.8.2 Dissonance. Another aspect of the acoustic structure of music that contributes to aesthetic experience, Brattico and Pierce 2013, is dissonance. Here, however, the evidence suggests that expertise sharpens the perception of dissonance and accentuates its negative effect on liking. For example, Biggin, Arncutt, and Rodal, 1996, found the greater tension-inducing effect of dissonant chords over consonant chords was more pronounced in musicians than in non-musicians. Other research has examined the pleasantness of melodic and harmonic intervals varying in dissonance, finding that musicians distinguish perfect consonants, imperfect consonants, and dissonance to a greater extent than non-musicians who tend to classify all intervals as moderately pleasant. Sean ETAL 2005. Similarly, dissonant chords are experienced as more unpleasant and minor chords as more sad by musicians than by non-musicians. Allison ETAL 2005, although fMRI showed no group differences in neural processing. Effects of musical expertise on responses to dissonance have also been found in physiological data. Delacherie, Roy, Hugo, Peretz, and Sampson, 2011, found that dissonant piano music induces more unpleasant feelings, valence, and stronger physiological responses, skin conductance responses, SCR, and zygomatic EMG, in musicians than in non-musicians, while musical training was a good predictor of valence. The conclusion that musical training reinforces the aversion to dissonance is supported by EEG and MEG research. Brattico and colleagues, 2009, report that the MMN response to dissonant and mistoned chords presented in the context of major chords is stronger for musicians than effects of expertise on processes involved in musical appreciation 331 non-musicians, and this varies as a function of degree of musical training, while no difference is observed in the response to minor chords in the same context. Sean and colleagues, 2005, also report qualitative differences between musicians and non-musicians in terms of neural processing of harmonic intervals varying in dissonance. These studies have focused on musical dissonances rather than sensory dissonance per SE. Because musically dissonant intervals are used, less frequently than consonant intervals, in the music that people listen to, these studies cannot discount the possibility that the effects are related to top-down cognitively driven expectations rather than bottom-up sensory dissonance. However, this is unlikely to be the case for the mistoned chords used by Brattico and her research team, 2009. Furthermore, at least one study has found that the effects of chord dissonance, an augmented triad, on verbs is clearly distinguished from the top-down cognitive effects of harmonic function discussed above, Rignall et al. 2001. 16.9 Conclusion drawing inspiration from Sloboda's 1991 definition of musical expertise as an emotional sensitivity to the music of a given culture. We have examined whether musical training affects aesthetic sensitivity to music. Contrary to predictions from the general literature on expertise, there is little evidence that musicians have more abstract representations of music, storing larger, more integrated chunks of music in memory, than non-musicians. There is also little evidence for any effects of musical training on emotional experience in general or on emotion recognition in music per SE. However, there is evidence that musical training leads to sharpened perceptual representation and processing and, in particular, the optimization of predictive models of musical structure. Importantly, much of the evidence for more accurate predictive models of musical structure in musicians comes from EEG and MEG studies, whose temporal precision allows detailed analysis of responses to individual musical events. Given that musicians are likely to spend significantly more time in focused listening to music than non-musicians, it is unclear whether this is an effect of music training per SE or simply increased musical exposure. What appears to be clear, however, is that musicians do tend to find pleasure in more complex music than non-musicians, at least in some circumstances, consistent with a Wundt curve shifted to greater levels of objective complexity. It is noteworthy that this effect of expertise on aesthetic experience occurs without any changes to emotional experience of music. It is tempting to associate this preference for increased complexity with the findings of more accurate predictive models, although robust, empirical evidence has yet to be developed. Somewhat paradoxically, it seems that musicians show greater sensitivity to dissonance in their aesthetic judgments than non-musicians. This enhanced sensitivity to perceptual qualities runs counter to a suggestion that experts might make greater use of knowledge-based criteria and less use of perceptual criteria than non-experts in their aesthetic judgments. Jesslyn 2013. It is, however, somewhat reminiscent of research in which visual experts show both greater configural processing and sensitivity to finer levels of detail than non-experts. 332 Marcus T. Pierce. One potential solution to this apparent paradox might be to suggest that dissonance introduces uncertainty that cannot be resolved through greater experience and training, while other aspects of objective complexity, e.g. harmonic syntax, metrical sophistication, can be rendered more certain with more accurate predictive models derived through experience and training. However, this would not explain why non-musicians appear to be less sensitive to dissonance than musicians. Another possibility, therefore, is that musicians have more accurate predictive models of musical consonance and dissonance and, as a result, generate greater prediction errors to dissonant tones and intervals. This would be consistent with their preference for greater complexity resulting from more accurate predictive models. There is clearly much work to be done. It is fundamental to link the development of accurate predictive models during musical training specifically to changes in aesthetic experience of music. Two differences in predictive uncertainty underlie the differential effects of training on different aspects of complexity, e.g. dissonance versus melodic complexity. How can we develop more general predictive computational models of musical structure that integrate melodic, harmonic, rhythmic, and timbral structure? It is puzzling that musicians fail to show greater sensitivity to high-level tonal form, but perhaps we are asking the question in the wrong way. It is possible that neurophysiological recording might prove more suitable to the task. Finally, the framework predicts that effects of training on predictive coding and aesthetic experience should be experience-specific. Therefore, we predict limited transfer between areas of musical expertise into other domains. As already noted, this is consistent with general findings in expertise research, Felhavishi et al. 2006. We have developed a framework for understanding the effects of expertise on aesthetic appreciation of music, facilitating hypothesis generation. Testing these hypotheses is likely to require a sophisticated combination of psychological study, computational modeling, and neuroimaging in which great care is taken to distinguish the causes and effects of musical training and distinguish these from general training effects and other factors that co-vary with musical training. Chapter 17 The Neuropsychology of Visual Art and Jan Chiturgi 17.1 Introduction Catherine Sherwood was 44 years old when she had a massive left hemisphere stroke. This catastrophic event left her with an aphasia and right-sided weakness. She was, and is, as at the time of writing this chapter, an artist and a professor. After recovering from the psychological impact and some of the neurological deficits from her stroke, she began to paint again using her left hand. She laid canvases horizontally, and moved around them in a mobile chair. She also noticed a curious thing. The style and content of her painting changed. Waldman 2000. She previously regarded herself as a particularly cerebral painter, approaching her work in an over-intellectual manner. After her stroke, she felt that images flowed from her more easily and expressively. Sherwood 2012, figure 17.1. Something changed about her process of making art. Chiturgi 2008. What had changed? More generally, cases like Professor Sherwood raise questions about what we can learn from the neuropsychology of art. Neuropsychology has been critical to advancing our knowledge of various cognitive systems, including perception, memory, and language, as shown by other chapters in this book. However, its impact on the study of aesthetics has been limited. Why? Certainly, an important factor is that its domain of inquiry neuroaesthetics is relatively immature. Chiturgi 2004b 2011. The data from which one might draw inferences are sparse. Beyond the constraints of limited data, fundamental questions about proper methods remain. It is easy to be seduced by the striking phenomenology and to construct interesting just so stories to account for these observations. Cognitive neurology and neuropsychology has had a long tradition of starting with careful clinical observations before applying rigorous quantitative methods to the phenomena under consideration. The neuropsychology of art is at this threshold and seems poised to make the quantitative shift. Chiturgi 2009. One could speculate that artists, by virtue of their developed visual motor skills, might be relatively protected from the visual motor deficits associated commonly with brain damage. Such speculation appears not to be true when we consider the effects of brain damage on artistic production. Boguslavsky and Bowler 2005, Chiturgi 2004a, 2004b, Rose 2006, Zadel 2005. Unilateral spatial neglect is a disorder in which patients are unaware of one side of space. Chiturgi 2003, Heilman et al. 1993. Artists with unilateral spatial neglect demonstrate neglect in their artwork. Bloom 1974. Visual agnosia is the inability to perceive or recognize objects visually. Artists with visual agnosia have difficulty depicting objects in their art. Wapner et al. 1978. Achromatopsia is the inability to apprehend color. 342 and Jan Chiturgi, A, B, figure 17.1 Examples of Catherine Sherwood's paintings. Permission obtained from Catherine Sherwood. A. Test sites, painted before her stroke. B. The cart before the horse, painted after her stroke. This material was originally published as visual art by Jan Chiturgi in the Roots of Cognitive Neuroscience, Behavioral Neurology and Neuropsychology, edited by Jan Chiturgi and H. Branch Coslet and has been reproduced by permission of Oxford University Press. For permission to reuse this material, please visit The Neuropsychology of Visual Art. 343 artists with achromatopsia may be unable to use color properly in their images. Sachs 1995a. In these cases, the artwork illustrates the nature of neuropsychological deficits. While the depictions may be beautiful and captivating, they do not offer insight into the nature of artistic production itself. In this chapter, I focus on two aspects of the neuropsychology of art. First, I will examine situations in which brain damage produces a paradoxical facilitation, chapter 1996, of artistic output. The effects of brain damage on the ability to produce visual art stand in sharp contrast to virtually all other complex human abilities. Diseases of the brain can impair our ability to communicate, coordinate movements, recognize objects, apprehend emotions, and make rational decisions. By contrast, while diseases of the brain often alter the ability to produce art, the alterations are sometimes interesting and occasionally even regarded as improvements, Chaturji 2006, but they can still be regarded as not impeding an individual's ability to create artworks. Second, I will discuss the issue of measurement in the experience of viewing art. One might approach the idea of measuring aesthetic experiences with some trepidation. The fear is that quantifying these experiences robs them of that which is fundamental to them. However, if neuropsychology of art is to advance as a science, it must incorporate some form of quantification in its methods, Chaturji et al. 2009. I will describe our attempts to do so. 17.2 The paradoxical facilitation of visual art. Implicit in a discussion of this paradoxical facilitation of art is the view that there is no single art center in the brain. Nor does one hemisphere play a privileged role in art production per se. Rather, the production of art is highly complex with different components mediated by different parts of the brain. The final artistic output emerges from a coordination of these different components. Brain damage alters the available parts of the brain dedicated to the overall artistic output that becomes the product of a different coordination of components. By analogy, we might think of these neural systems like a suspended mobile. The mobile rests still in the equilibrium of its weights. If a particular weight is removed, the entire configuration might collapse. However, the configuration might also find itself in a new resting state that is different from the original but which is also appealing. Similarly, brain damage may render an artist incapable of continuing to work, or it may create a new equilibrium in which the individual's artistic work proceeds in new and interesting configurations. There are 4 ways in which neurological disorders might change and sometimes improve art production, Chaturji 2006. These are they: 1. Disposition to produce visual art, 2. Provision of a unique visual vocabulary, 3. Aids to descriptive accuracy, and 4. Changes in expressive powers. 17.2.1 Disposition to produce art. Frontotemporal dementias, FTD, are a group of degenerative neurological diseases which cause people to undergo profound changes in their social interactions. They can become disinhibited and disorganized. They can have problems with language, attention span, and the ability to make decisions. In addition to these alterations in personality in 344 and Chaturji cognition, a few people with FTD develop a propensity to produce art for the first time. Miller and colleagues, Miller et al. 1998, note that these people's art is realistic, not abstract or symbolic. It is highly detailed and has an obsessive quality. The patients themselves seem intensely preoccupied with their work. The artistic output of people with FTD appears to be a consequence of changes in their personalities. The acquired obsessive-compulsive traits find graphic expression and they produce striking visual images as a part of their repetition and attention to detail. Several other examples show that obsessive-compulsive traits rendered by neurological diseases can predispose people to produce art. Sachs, 1995b, described the Italian painter, Franco Magnani, living in San Francisco. Magnani painted hundreds of realistic scenes of an Italian town, Pontito, where he grew up. At the age of 31, Magnani probably had an encephalitic illness. Following that illness he painted compulsively. Pontito preoccupied his thoughts and conversations. Sachs speculated that he had partial complex seizures and was in part demonstrating an obsessive sticky personality sometimes associated with temporal lobe epilepsy, Waxman and Gishwin 1975. Such patients are also sometimes hypergraphic, meaning they read incessantly. Magnani's hypergraphia was being expressed visually rather than verbally. Lithgow and colleagues, Lithgow et al. 2005, reported the case of a builder with a subarachnoid hemorrhage. He also had no interest in art premorbidly but became an obsessive artist after recovery from the initial injury. After the hemorrhage, he had a normal verbal and performance IQ and exhibited behavioral patterns except for some degree of verbal disinhibition. He did well on most neuropsychological tasks except for those that involved mental flexibility. He also began to draw hundreds of sketches, mostly of faces. He then moved to large-scale drawings, sometimes covering entire rooms, while confining his art to a few themes. Finally, about 10% of children with autism develop savant-like abilities, Rimland and Fien 1988. A subset of these children produce striking visual images, Sachs 1995c. The most detailed description of such a case was Nadia, reported by Self, 1977. As a baby, Nadia did not respond to her mother and as she got older she lacked social empathy. As a child, she was obsessively concerned with the presence of other children without forming any substantial bonds with them. Her acquisition of language was delayed. Despite these developmental abnormalities, she was remarkably skilled at drawing. By the age of 3 years she was drawing lifelike horses. She drew intensively for a few moments at a time, always copying images. She also focused on specific images, like horses, of which she drew hundreds of examples. While Nadia's abilities were striking, she was not unique. Autistic children with these striking drawing skills seem to focus on specific subjects and draw them repeatedly. Thus, neurological disorders that produce obsessive-compulsive traits can also dispose people to produce art. These artists produce realistic images and focus on a narrow range of themes. While the neural basis for obsessive-compulsive disorders is not completely understood, dopamine and alterations of reward circuits are probably involved. We reported a patient with Parkinson's disease who produced art obsessively after being placed on dopamine agonists, Chaturji et al. 2006. Interestingly, despite profound impairments in his motor control, which were evident when he wrote, he could make graceful sinuous the neuropsychology of visual art 345 movements when drawing. Obsessive-compulsive traits are also associated with dysfunction of the orbitofrontal and medial temporal cortices and frontostriatal circuits, Kwong et al. 2003, Saxon et al. 1999, Percy et al. 2003. Notably, in cases such as those described in this section, these regions may have been damaged, leaving posterior occipitotemporal cortices intact. The preservation of posterior cortices ensures that the neural substrate that represents faces, places, and objects are preserved and are available as the focus of these patients' obsessions. 17.2.2 Visual vocabulary. Neurological disorders such as migraine and epilepsy are associated with productive visual phenomena. Of over 200 entries submitted to the first national art competition sponsored by the British Migraine Association and WB Pharmaceuticals, 70% showed spectral appearances, 48% showed fortifications, 16% showed areas of visual loss, and 2.5% showed mosaic visions. Wilkinson and Robinson 1985. The artist, Ignatius Brennan, Caudal and Robinson 2000, eloquently expressed how migrainosaurus inspired his art. His migraines, beginning at the age of 11 years, were experienced as frightening episodes of visual loss, often with a zigzag cloud obscuring much of his visual field. As he got older, he saw triangles and rounded forms as well as mosaics. He also experienced visual distortions of things getting larger or smaller. He recounts the effects of migraines on his art as follows. I started with pictures of my migraine experiences unconsciously rather than deliberately, when I was in art school. I used to do a lot of drawings of landscapes at that time and often found that I would be drawing clouds not just in the sky, but everywhere, which I think was a reference to the visual voids experienced during visual loss. I also used serrated zigzag shapes in my drawings, symbolizing the experience of a whole being broken up. Clouds, zigzags and other imagery are part of my own personal visual vocabulary, but which certainly has come out of my brain experiences. I'm absolutely sure. I don't tend to do that deliberately, but when it suits a particular subject, e.g. to represent a feeling or an emotion, I make use of these images in different ways. Such patients offer insights into how artists generally have a visual vocabulary at their disposal. Greater analyses of these cases may inform us about how artists develop this visual vocabulary and how they develop a visual grammar in concatenating this visual vocabulary. 17.2.3 Descriptive accuracy. For centuries, visual artists have been preoccupied with rendering objects and their surroundings accurately. Underlying the problem of descriptive accuracy in drawing and painting is the role of knowledge. Visual agnoses are a class of disorders in which patients have difficulty recognizing objects. Farrer 1990. Since Lissauer's classic descriptions of visual agnoses, object recognition deficits are known to lie on a continuum between perceptual and conceptual deficits. Lissauer 1890. Perceptually based agnoses, called apperceptive agnoses, impair the ability to process the visual information into a coherent 346 and Jan object. Conceptually based agnoses, called associative agnoses, involve impairments of semantic knowledge of the object. Farrer 1990. Wapner, Judd, and Gardner, 1978, described an artist with an apperceptive agnosia who had difficulty copying images despite being able to convey depth and shading in drawings that were otherwise fragmented. His preserved semantic system did not help guide his artistic production. Thus, when asked to draw a telephone, he constructed images by reasoning. It needs a base for it to stand on, a place to speak into, something to hear with a wire to plug in for communication, and a place to dial. This verbal strategy was not effective in rendering accurate images. Semantic knowledge by itself does not help render objects accurately. This patient contrasts with two people with associative agnoses, Franklin et al. 1992, Schwartz and Sholov 1990. In both cases, when asked to draw objects from verbal labels, these people drew crude, simplified images similar to those drawn by a young child. However, when drawing from complex visual images, the results were strikingly different. For example, one of these people could copy a portrait originally painted by Botticelli or draw a beautiful portrait of a staff worker, Franklin et al. 1992. People are thus able to render objects accurately and beautifully without semantic knowledge. The case of the Polish aphasic artist also informs us about the relationships between semantics and art, Kaczmarek 1991. Profoundly influenced by the events of the Second World War, his pre-morbid paintings were anti-war statements. They often included numbers, letters, and ideograms. Following his stroke, he could only produce a few words. At its core, our semantic system functions to abstract and generalize. The use of abstracted symbols could be considered a marker for a preserved semantic system. Although testing of his semantic system was not reported, from the descriptions of his aphasia one might infer that it was impoverished. His inability to make use of verbal symbols extended to his artwork. He was no longer able to produce paintings in his previous style of using symbols to communicate his anti-war sentiments. However, he was still able to draw realistic landscapes and portraits well, despite having lost his ability to manipulate symbols. Does semantic knowledge of an object hinder artistic production? The art historian Ernst Gombrich, 1960, observed that even trained artists impose knowledge of what they are looking at in their depictions in a way that can compromise their accuracy. Thus, impaired knowledge, provided visual motor systems are intact, might aid in the ability to depict objects and scenes accurately. Perhaps such impaired knowledge accounts for cases of autistic children with savant-like artistic abilities. Autistic artists need only to look at an object for a few minutes before being able to draw them rapidly and accurately. Sachs 1995c, Self 1977. Nadia's abilities were not an accelerated version of other children's drawing development. She did not first pass through a phase of drawing simple schematic images before learning to draw realistically. Rather, her skills developed very early and did not change much over time. Nadia initially drew horses deftly and without hesitation. Two observations suggest that she treated horses as visual patterns rather than as objects. First, she would start drawing anywhere on the page. Rather than trying to squeeze the whole horse into a page, she would stop drawing when the neuropsychology of visual art 347 she came to the paper's edge even if it meant only drawing part of the horse. Secondly, most people draw horses by starting at the head. Nadia could start her drawing at the neck and seemed unaffected by critical features associated with a specific object, such as the head of a horse. Her remarkable skill at drawing horses, and later pelicans, was not hindered by semantic associations that interfere with the ability to see the visual object. As Nadia eventually acquired language, her drawings became more prosaic. Presumably, the acquisition of language indicated development of a richer semantic system and detracted from her artistic skills. 17.2.4 Changed expressivity. Visual art is of course not restricted to rendering objects and scenes accurately. Perhaps driven by the advent of photography, visual art diverged into many forms of expression. Among the most intriguing effects of brain damage on artists are a class of phenomena in which the inability to make accurate depictions results in surprisingly appealing stylistic changes. These changes can occur in the use of color and form and in the content of images. Sachs, 1995a, described an artist with an acquired achromatopsia following a traumatic brain injury. His earlier paintings were colorful and abstract. After the accident, everything appeared dirt gray to him. His initial attempts to use color did not work and he resigned himself to painting in black and white. Eventually he incorporated a limited set of colors in his paintings. After an initial sense of helplessness, he considered his new way of seeing as a strange gift. He thought he saw the world as pure form, uncluttered by color, and endowed with a new range of expressions. Right hemisphere damage can produce left spatial neglect, and artists with neglect omit the left side of images that they draw or paint. Lang et al. 2003, Cantagallo and Sala 1998, Halligan and Marshall 1997, Jung 1974, Marsh and Fullman 1987, Schneider et al. 1993. As they recover from their neglect, their use of line may still be altered. Two examples show how this change in the use of line can produce art that is highly regarded. Lovis Corinth, an important German artist, had a right hemisphere stroke in 1911. As he recovered, he resumed painting. His self-portraits and those of his wife showed clear changes in style, with details on the left sometimes omitted and textures on the left blending with the background. Alfred Kuhn characterized this work as follows, quoted in Gardner 1975: Corinth had become prescient for the hidden facets of appearance. The contours disappear, the bodies are often as root asunder, deformed, disappeared into textures. Also the faithfulness of portraits has ceased almost entirely. With white stripes the person is captured in essence. Characterization is now exaggerated, indeed, often to caricature. Corinth always seems to be painting a picture behind the picture, one which he alone sees. At this point Corinth shifted from the ranks of the great painters into the circle of the great artists. Heller, 1994, reported the experience of the artist Lauren Hughes, who after a right hemisphere stroke had difficulty coordinating the spatial relationship between lines. This forced her to abandon her pre-morbid style of accuracy and realistic depiction. Instead she turned to her own imagination and emotions. Initially, she was too ashamed to display 348 and Jan her paintings, but she began to show publicly once she became comfortable with her new style. The artistic community responded well to these distorted images. The critic Eileen Watkins described her work as now delivering an emotional wallop that was not present previously. When they occur as a result of left brain damage, stylistic changes might be different from those observed stemming from right brain damage. The specific changes reported are the introduction of more vivid colors and a change in content. These changes are exemplified in the Bulgarian painter, Slavoj Boyajev, the Californian artist Catherine Sherwood who was mentioned in the introduction, and a Swiss painter reported by Anoni and colleagues. Boyajev's pre-morbid artistic style was natural and pictorial and he tended to use earth tones in his paintings. Following the onset of his aphasia, Boyajev's paintings have been described as richer, more colorful, and containing more fluid and energetic lines. Brown 1977, Zemov et al. 1969. The imagery in his work became more inventive and at times even bizarre and fantastical. Similarly, Catherine Sherwood suffered a left hemisphere hemorrhagic stroke that left her with aphasia and right-sided weakness. Waldman 2000. She trained herself to paint with her left hand, and since then her career has flourished. Premorbidly, her images were described as highly cerebral, incorporating a range of esoteric images such as cross-dressers, medieval seals, and spy photos. After her stroke, she felt that she could not produce these images even if she tried. Her new style is described as raw and intuitive, with large irregular circular movements. She says her left hand enjoys an ease and a grace with the brush that her right hand never had, and describes it as unburdened. Sherwood 2012. Finally, Benoni and colleagues, 2004, recently described the Swiss landscape painter whose art was described as being figurative impressionist. He had a small stroke in the left thalamus. His wife thought he had mild emotional dysfunction after his stroke. He felt that he was more sensitive to the hidden beauty of images and used bolder colors. He switched from realistic to more impressionistic images. He thought that he was less likely to use lines, contours, and perspective clearly and felt that he was more creative. A final stylistic change rendered by brain damage is a move towards simplicity. Benoni and colleagues, 2004, described a person with a left occipital lesion. A month after his stroke he resumed drawing and painting. His new artwork was simplified, stylized, increasingly abstract, and confined to a limited use of colors. It is not known if damage to visual association cortices would consistently result in simplification and abstraction. A few artists with Alzheimer's disease have continued to paint, Crutch et al. 2001, Moore and Pervulovic 2004, Miller and Ho 2004, and demonstrate a similar pattern. William U. Termelin painted a series of self-portraits several years into the course of his illness. As these portraits became increasingly simplified and distorted, they appear as haunting psychological self-expressions. Willem de Kooning is probably the best-known artist who continued to paint after the onset of Alzheimer's, Store 1995. De Kooning's ex-wife and students provided the structure for him to continue to work. They stretched his canvases and mixed his colors. Experts in neuropsychology of visual art 349 think this late period represents a new and coherent style. His paintings were simpler and he confined his palette to primary colors. Traces of shapes from earlier works are evident, but are pared down. Gary Garrels, 1995, the senior curator at the San Francisco Museum of Modern Art, thought the vocabulary of forms was retained, but clarified. The results are paintings of an openness and freedom not seen before, paintings that are extraordinarily lyrical, immediately sensual, and exhilarating. 17.3 Quantification in the neuropsychology of art. Despite the fascinating observations recounted here, much needs to be done if neuropsychology is to make substantive contributions to empirical aesthetics. For the field to mature, it must move beyond recounting interesting anecdotes. Methodologically, it is critical to quantify features of artwork in order to assess change. Most of the cases reported are devoid of measurement. Claims about changes in art after brain damage are usually post hoc comments supported by a few illustrative examples of artwork. We need an instrument to assess art quantitatively. Such an instrument should have at least two characteristics. First, it should assess artwork by a comprehensive set of attributes which would include formal properties, use of line, color, composition, etc., and content properties, abstract, realism, etc. Second, it should distinguish between descriptive and evaluative judgments. With such an instrument one could begin to impose quantitative structure on otherwise casual observations about works of art. With these considerations in mind, we developed the assessment of art attributes, AAA, Chaturji et al. 2010. The AAA assesses 12 descriptive attributes that would apply to any piece of visual art. 6 attributes refer to formal/perceptual properties and 6 to content/conceptual properties. The 6 formal/perceptual attributes are balance, color saturation, color temperature, depth, complexity, and stroke style. The 6 content/conceptual attributes are abstractness, animacy, emotionality, realism, representational accuracy, and symbolism. The stimuli in the AAA consist of 24 paintings from the Western canon. These are paintings by well-known artists, but not their most famous works, and encompass a range in the 6 formal/perceptual and 6 content/conceptual attributes of interest. The paintings are also evaluated for preference or liking in their level of interest for the viewer. 17.4 Art production. We have used the AAA to examine changes in art production as well as art perception following brain damage. For art production, we examined the work of 3 artists that have already been mentioned, Chaturji et al. 2011. These are Sherwood and Boyajev, both with left brain damage, and Corinth with right brain damage. In each case we sampled several paintings completed before and after the stroke occurred. Average ratings on each attribute were obtained for each painting. Then the average ratings for all the pre- and post-morbid paintings were obtained for each participant for each artist. We examined Sherwood and Boyajev's work to determine if left brain damage produces consistent changes in art. Sherwood describes her approach to her work pre-morbidly 350 and Jan Chaturji as over-intellectualized, Chaturji 2008. Post-morbidly, her work has been described as raw and more expressive, and less forced, Sherwood 2012. In concordance with these descriptions, raters found her work following brain injury to be more abstract, more symbolic, more distorted, more vibrant, less realistic, and depicted with looser strokes. Raters also found her work to be flatter and to contain warmer colors, changes not mentioned previously by critics describing her work. Boyajev's work has been described as becoming fantastic and sometimes bizarre with richer, more colorful forms, and having fluid, energetic lines. Brown 1977. Consistent with these descriptions, raters found his work to be more abstract, more symbolic, less realistic, more distorted, as well as having a looser stroke style. They also found his work to be flatter and less animated, changes also not mentioned by critics before. Could motor deficits for Sherwood and Boyajev have caused these changes? Both were right-handed artists who began to paint with their left hands after their strokes. From these data, it is not clear if some pictorial aspects of the artwork, such as the coarser brush strokes, changed because of hemispheric brain damage or because they began to use their left hand. However, a shift to the left hand is unlikely to explain the use of increasingly vibrant colors or changes in conceptual attributes of their artwork, such as greater symbolism or abstraction. A priori, one could be pessimistic about the prospects of identifying systematic effects of brain damage on art production. After all, artistic styles and content vary so much across different artists that one might be comparing changes in qualitatively different kinds of objects. Our observations of Sherwood and Boyajev's paintings suggest that this pessimism might not be warranted. Sherwood and Boyajev's artistic styles are quite different from each other. For example, Sherwood's paintings started out being substantially flatter than Boyajev's. Critically, both artists' paintings were judged as becoming flatter following their strokes, despite the fact that Sherwood's paintings executed before her stroke were more similar to Boyajev's paintings made after his stroke in depicting death. Thus, it would be a mistake to think that people with left brain damage produce a prototypic style of painting. Rather, it appears that left brain damage produces a prototypic shift in style of painting. Sherwood and Boyajev's paintings became more abstract, symbolic, and distorted as well as less realistic, and they were painted with looser strokes, more vibrant colors, and less depth. Chaturji et al. 2011. Examining Corinth's work would test the specificity of these changes. Corinth's paintings after his stroke were described as deformed, and attempts at producing faithful portraits ceased almost entirely. Lang, 2006, described the broadening of brush strokes, a lack of depth, less spatial detail, and several deformities depicted on the left side of his self-portrait paintings. Researchers found Corinth's paintings to be more abstract, more distorted, less realistic, and also to exhibit looser strokes and a flatter perspective. When Sherwood, Boyajev, and Corinth's paintings are considered together, the following changes were found in all 3 artists' works. Their paintings became more abstract and distorted and less realistic and accurate. They were also rendered with looser the neuropsychology of visual art 351 strokes, less depth, and with more vibrant colors. Thus, none of these changes can be ascribed to laterality of brain functions. Also, their paintings did not change in complexity or the level of emotion being conveyed. It remains to be seen whether these attributes would be susceptible to change with other kinds of neurological illness. For example, we might expect the artworks of people with Alzheimer's disease to become less complex over time. All the changes observed in Corinth's paintings were also observed in works by both Sherwood and Boyajian, Chatterjee et al. 2011. Thus, chronic right hemisphere damage does not appear to produce specific patterns of change in artistic production. By contrast, both Sherwood and Boyajian's subjects became more symbolic. This could mean that artists with left brain damage, because of an unfettered right hemisphere, engage meaning more loosely, specifically in the use of symbolism. These data show that the popular idea that right hemisphere is the artistic hemisphere is wrong. Clearly, both hemispheres participate in artistic production as shown by the fact that these artists' paintings changed regardless of which hemisphere was damaged. If anything, damage to the left hemisphere produced more significant alterations in artistic production than did damage to the right hemisphere. We have also used the AAA to assess gradual changes in artistic styles in 2 patients with Alzheimer's disease, AD. Investigating artists with AD allows us to look for gradual changes in art production rather than sudden changes brought about by a stroke. William Mutermelin was diagnosed with AD after a long, successful painting career, Crutch et al. 2001. He was born in Philadelphia and studied at the Pennsylvania Academy of Fine Arts from 1951 to 1957. He moved to England in 1957 where he enrolled at the Ruskin School of Art in Oxford before settling in London. His early work was characterized by linear expressionism, with frequent inclusion of pop imagery and styles, including a use of strong colors. His earliest symptoms began 4 years before diagnosis, and involved difficulties with tying a necktie, calculating household finances, and memory of day-to-day events. Formal neuropsychological examination revealed a moderate degree of global cognitive deterioration, while MRI indicated generalized cerebral atrophy. Following the initial diagnosis at the age of 61, regular clinical assessments documented the expected gradual decline in cognitive function, Crutch and Rossa 2006. We looked at 5 self-portraits executed by William Mutermelin in the 4-year period following his diagnosis. The second artist, Lester Potts, was diagnosed with Alzheimer's disease around age 70. He had worked in a rural Alabama sawmill during the Great Depression. He served in the Korean War and was regarded as a dependable civic leader. He had not painted before his enrollment at an adult daycare center. At the center he was taught to use watercolors by a retired artist as part of a community outreach program. By the time he died at age 78, Lester Potts had painted over 100 original watercolors. Using the AAA, we found that both artists' paintings became more abstract and more symbolic, less realistic, and less accurate in depicting figurative detail. Potts' paintings also showed more color saturation, shifts in hues, less complexity, and less emotion as his disease progressed. Notably, changes were not seen with balance, depth, or stroke quality in either person's paintings. 352 and Jan Chatterjee, our observations were in general accord with other observations of the relationship between AD and artistic production and offered greater detail in the nature of change observed. For example, Fornes 3, 2005, described changes in the portraiture of a woman who suffered from AD. These changes include trends toward unusual figure font, loss of proportion in the facial features, and loss of proportionality. The changes mentioned might parallel those observed in Mutermelin and Potts. Unusual figure font and loss of proportionality might correspond to a decline in depictive accuracy. However, it is not clear if loss of proportionality could refer to loss of balance, which we did not see in either person. This uncertainty highlights one of our points, which is that clear operational definitions of art attributes are needed if we are to compare results across studies. Our findings also validate anecdotal observations of changes in abstraction and increased symbolism among artists with AD. Crutch et al. 2001, Cummings and Zarrett 1987, Rankin et al. 2007, Chatterjee 2004a. For example, art historians describe a heightened trend towards abstraction in paintings executed by Willem de Kooning during the progression of his AD. Garrels 1995. Moore and Pervulovic, 2004, thought that in the later works of the painter Carolus Horn, ornamental symbols and mythical creatures appeared, which were derived from a conjunction of different species. Cummings and Zarrett, 1987, reported that an artist with AD over a period of 2.5 years moved towards simplicity and distortion. Miller and Hill, 2004, observed AD artists to produce works with less precision and attention to spatial relationships. 17.5 Art perception. We know virtually nothing about the neuropsychology of the perception of art. One might expect that sensitivity to different attributes within a work of art would be affected by different kinds of brain damage. Recently, we used the AAA to examine the effects of brain damage on art perception, Romberger et al. 2011. Our investigation focused on the role of the right hemisphere. The right hemisphere participates prominently in visuospatial attention and representation, Chatterjee 2003, Heilman et al. 1993. As a first step, we wish to avoid confounding language comprehension with perceptual judgments in our study. For example, if a participant does not understand what the word symbolic means, it would not be difficult to assess their perception of symbolism in any painting. We also use contemporary lesion analysis methods in our study. Voxel-based lesion symptom mapping, VLSM, techniques allow us formally to assess the way in which damage to a brain area correlates with behavioral scores. Bates et al. 2003, Timurg et al. 2007, Wu et al. 2007, with the advantage that one does not have to establish a deficit cutoff. Rather, behavior in VLSM considered a continuous variable. In this study, the judgments of 20 people with right brain damage were compared to 30 healthy age-matched control participants. Of all the content/conceptual qualities, damage to the right frontal lobe was associated with differences in judgments of abstractness, realism, animacy, and symbolism in visual art. In addition, damage to the right parietal lobe was related to deviations in judgments of animacy and symbolism. There were no the neuropsychology of visual art 353 brain behavior relationships for differences in evaluative judgments, those of preference or level of interest for the viewer. Any aesthetic experience is built upon at least 3 components, Chatterjee 2004b, Chatterjee 2011. These components are the experience of sensory qualities, the associated sets of meanings, and the emotional responses evoked by the aesthetic object. Broadly, one might regard the formal perceptual attributes of the AAA as probing the sensory experience, the content conceptual attributes as probing the meaning, and the evaluative questions as probing the emotional response to these paintings. The data from this study suggests that these 3 components of visual aesthetic experiences might segregate broadly in the organization of the brain. Most of our participants had damage in the distribution of the right middle cerebral artery. This distribution of brain damage involving lateral frontal parietal and temporal cortices was more likely to affect judgments of conceptual attributes. We would predict that damage in the posterior cerebral artery distribution affecting ventral occipital and temporal cortices might be more likely to affect the perceptual attributes. Furthermore, given the extensive data implicating the ventral striatum and orbitofrontal cortex and subjective rewards, Cable and Blincher 2009, damage to ventromedial prefrontal cortices is plausibly more likely to affect people's evaluation of paintings. These recent results demonstrate the feasibility of conducting systematic quantitative studies in the neuropsychology of art. This point by no means implies that theoretical analyses or qualitative approaches to art are not useful. It does mean that if the neuropsychology of art is to mature as a science, it needs to incorporate quantitative approaches and formal tests of hypotheses as part of its research program. 17.6 Conclusion. In reviewing the literature of the neuropsychology of art production, I emphasized the possible enhancing effects of brain damage on artistic production. Of course, these observations are based on selected artists. It is likely that many more artists are devastated by their brain injury and these cases are not reported. We simply do not know the base rate of facilitation effects. Yet, the examples of changed and possibly improved art following brain damage point to the multifaceted nature of art. In my view, exploring the mechanisms underlying the alterations and gaining insights into these facets is one way that neuropsychology can advance neuroaesthetics. Looking forward, unless the neuropsychology of art can incorporate the basic rigors of any experimental science, we will not get past the description of seductive artistic phenomenology under consideration. We are in a position to augment qualitative insights with quantitative approaches. The observations from patients can also serve to generate hypotheses to be tested using functional imaging techniques. For example, the hypothesis that the perception of art dissociates from the evaluation of art is amenable to functional imaging methods. We can be guardedly optimistic that the neuropsychology of art may mature and serve as a fundamental anchor in the new field of neuroaesthetics. 354 and Jan Chatterjee 18.1 Introduction. While many researchers studying the neuroscience of aesthetics are primarily interested in describing how healthy brains create, produce, and appreciate art, there is much to learn from individuals whose neurological illnesses alter their artistic output. In particular, there are rare cases of patients whose art gains greater critical acclaim as their neurodegenerative disease progresses. Miller et al. 1998, Chakrabarty 2011. These unique patients provide illuminating glimpses into the brain regions that underlie creativity, as well as insights into what aspects of art are appreciated by specialists and the general public. Increasingly, neuroscientists are conceptualizing mind-brain relationships in terms of circuits of brain regions that work together to create thoughts, feelings, experiences, and actions, rather than focusing on a single area of the brain. In line with this trend, clinician scientists characterize neurodegenerative disorders with respect to which circuits are affected by disease. This characterization is also useful when it comes to a discussion of the neural underpinnings of artistic production because producing art is a multifaceted task, demanding the participation of many distinct brain regions. A comprehensive model of the neural basis of creativity remains elusive in part because defining and measuring the value of art is subjective. While most researchers agree that creativity involves producing ideas or products that are both novel and useful, this definition is more difficult to apply to the production of visual art than to creative cognition or other manifestations of creativity. Here, the goals of science and art clash. While science is used to extract general rules or principles about the world, art is by its very nature subjective, designed to use the individual experience to demonstrate what is universal. Therefore, this chapter will focus both on studies of groups of patients and healthy individuals and exemplary case histories that provide additional insights into our capacity to produce art. 18.2 The path of degeneration in dementia. Neurodegenerative diseases that cause dementia begin with the aggregation of misfolded proteins in specific parts of the brain. Pic 1892, Alzheimer 1911. These misfolded proteins cause neurons to malfunction and die, and there is evidence to suggest that degeneration spreads via functionally connected brain areas. Joe et al. 2012, such that each 358 and Revis Quintus and Sozi neurodegenerative disease targets a different network of these regions. Seeley et al. 2009. Thus, each disease recapitulates unique constellations of symptoms that reflect the functions of the affected neural circuits. Seeley et al. 2009, Joe et al. 2010. Clinical examination results in classification of neurodegenerative diseases based on symptoms and physical examination findings. Neuropathological examination enables neurodegenerative diseases to be classified based on characteristics of disease proteins seen under microscopy. Diagnoses of clinical and neuropathological examinations, however, do not always concur in individual patients. Since the majority of the scientific literature on neurodegenerative disease and creativity is based on clinical classifications, this chapter will primarily use clinical characterizations. We will focus on Alzheimer's disease, AD, the most common neurodegenerative disease, and frontotemporal dementia, FTD, a common dementia in those under 65 years of age. Common diseases with Parkinsonism include Lewy body disease and Parkinson's disease, progressive supranuclear palsy, and corticobasal degeneration are rare. FTD is further classified into behavioral variant FTD, BVFTD, and two progressive disorders of language known as primary progressive aphasia, PPAs, including semantic, SVPPA, and non-fluent, NFPPPA, variants, Gorno-Tempany et al. 2011. Before inferences can be drawn regarding the general effect of neurodegeneration on artistic proclivities, a characterization of each disease is useful. Alzheimer's disease most commonly starts with short-term memory loss. As the disease progresses, other cognitive functions decline, including planning and organizational abilities, executive functions, language, and visual perception. People with early onset AD may initially have relative sparing of short-term memory, with language or visual skills affected first. AD affects the medial temporal, parietal, and occipital lobes. In the earlier stages of AD, cognition for social norms and emotional function remains intact. By contrast, BVFTD is characterized by prominent early behavioral or personality changes. Apathy, loss of empathy, rigid personality, obsessions, and compulsions occur. Patients with BVFTD harbor right frontal insula, anterior cingulate, and orbitofrontal damage. The PPAs both manifest in progressive loss of language function. On the one hand, in SVPPA, speech is fluent and grammatical, however loss of words and object meaning occurs. Patients with SVPPA initially have early degeneration in left anterior temporal lobes, however, disease eventually spreads to the right anterior temporal lobe, resulting in personality changes and trouble recognizing faces. On the other hand, NFVPPA shows agrammatical, effortful speech with vowel distortions, thus disruptions in language and speech production occur. Most affected regions in NFVPPA include left inferior frontal cortex, see table 18.1. Alzheimer's disease is sometimes referred to by neurologists as targeting the posterior brain, since early degeneration is often seen in parietal and occipital lobes, particularly in people with early onset disease, and one of the early signs of the disease is an inability to copy complex figures. Thus, visual art, as produced by patients who suffer from AD, is often degraded, in terms of visual complexity and technique. Rankin et al. 2007. In contrast, patients with neurodegenerative disease whose artistic production increases what seems to improve with the creation of art in the setting of dementia 359 disease progress, tend to have posterior regions intact, and damage, at least initially, localized in the anterior portion of the brain. Miller et al. 1998. 18.3 The emergence of art in the setting of dementia. The study by Miller and colleagues, 1998, was among the first observations that certain neurodegenerative diseases might lead patients to engage in creative endeavors. The study describes 5 patients suffering from FTD who developed artistic skills during the early stages of the disease. The authors found that while AD is a far more common dementia, most, if not all the patients they observed who developed artistic prowess after the onset of dementia, were diagnosed with FTD. In addition, patients' artistry was manifested in the visual, and never the verbal domain. These patients developed skills in painting, photography, or sculpture, and most of the work they produced was realistic, rather than abstract or symbolic. See figure 18.1. Miller and colleagues, 1998, observed that the art seemed to result from previously seen images that were recalled even when patients had lost the ability to describe the images using language. The artists, while losing most other cognitive and social functioning, showed increased attention and fascination with details of faces and objects, as well as sounds. This study sparked an interest in exploring how degeneration of particular brain regions might release or enhance latent artistic abilities. Spurred on by the discovery of the 5 patients mentioned above, Miller and colleagues, 2000, conducted a larger study on the emergence of artistic talent in patients with FTD. They included 69 patients diagnosed with FTD and found 12 who acquired or maintained artistic skills in both musical and visual domains. Like their original 5 patients, these patients showed skills that were not reliant on language, and their work lacked a symbolic or abstract component. 8 of the 12 patients had SVPPA comprising almost 50%, 8/17, of all patients studied with this variant. 3 more had predominantly temporal degeneration as evidenced by imaging or perfusion, although they had frontal degeneration later on in the disease. The authors note that degeneration of temporal cortex coupled with sparing of frontal functioning was a characteristic feature of all patients who showed artistic ability. 9 of the 12 patients showed predominantly left hemisphere pathology, while only 1 showed bilateral degeneration. Indeed, patients with asymmetrical degeneration resulting from frontotemporal lobar degeneration, FTD, seem to be more likely to show changes in creative behavior with Table 18.1 anatomical systems involved in earlier stage AD and FTD neurodegenerative disease. Anatomical regions affected: Alzheimer's disease, entorhinal cortex, hippocampus, parietal and occipital lobes, behavioral variant FTD right frontoinsula, anterior cingulate cortex, orbitofrontal cortex, semantic variant PPA left right, anterior temporal poles, non-fluent variant PPA left, inferior frontal gyrus, operculum, 360 and Revis Cantus and CDE disease than those who have symmetrical damage. That is, BVFTD patients tend to show somewhat more symmetrical involvement of disease processes across regions of the frontal lobes, whereas patients with SVPPA tend to show atrophy that begins unilaterally, only spreading to the contralateral hemisphere late in the disease. Johnson et al. 2005. Interestingly, 4 out of the 5 artistic patients that Miller and his team, 1998, studied had SVPPA, not BVFTD. Of the 4 patients diagnosed with SVPPA, 3 showed more degeneration of the left and the right temporal cortex either in SPECT or postmortem pathology. 18.4 left versus right brain thinking, deciphering the neural basis of creativity by studying neurological or psychiatric patients has a long history, although the focus has been on loss rather than on gain or release of latent talent. This same history has led to the proliferation of several oversimplifications and myths. Arguably, the most popular myth to date is the hemispheric asymmetry hypothesis. Simply put, proponents of the hemispheric asymmetry hypothesis suggest that creativity is localized primarily in the right hemisphere, while the left hemisphere impedes or blocks O's for octopus. From an ABC book of invertebrates, and Adams 2004 masks Jansi Chong 2000 untitled Fountain Lee due to 1970 Fishes Carol Franz 1999 figure 18.1 samples of artwork by patients towards the end stages of dementia. Reproduced from The Creation of Art in the Setting of Dementia 361 Creative Thought. This hypothesis relies on the idea that the two cerebral hemispheres are functionally dissociable, with different cognitive processes either wholly or largely localized to one or the other side. The hemispheric asymmetry hypothesis with respect to the brain basis of creativity also has a long history, one that stretches back to the turn of the 20th century. At this time, modern psychology was in its infancy. Psychiatrists were investigating the possibility of multiple personalities residing in different brain regions, and neurologists were finding that certain functions were localized in one hemisphere or the other, as patients with unilateral neurological insults were demonstrating. The dual nature of the brain inspired fiction, such as the famous tale of Dr. Jekyll and Mr. Hyde by Robert Louis Stevenson. It has long been known that aspects of visuospatial cognition are localized in the right hemisphere, including the perception and manipulation of forms and their spatial relationships. Hecka and et al. 1962. Deficits in visuospatial cognition are typically demonstrated by examples of visual agnosia, the inability to recognize or identify visual stimuli. A particularly striking example of visual agnosia is prosopagnosia, or the inability to recognize faces. In short, visual agnosias are not thought to be due to deficits in primary sensory capabilities, but rather in secondary and associative processing of visual information. That is, agnosias reflect deficits in visuospatial processing. The affected individual is aware of the visual stimulus but cannot process the relationships between its features, thereby causing an inability to recognize the object. Hecka and colleagues, 1962, looked at over 400 patients with lesions of the posterior parts of the brain and found that in most cases, disorders of visuospatial abilities were associated with right hemisphere insults. 51 of 59 cases of visual agnosia were right hemisphere lesions, while 16 of 22 cases of prosopagnosia were in patients with right hemisphere damage. Similar conclusions can be drawn from several studies conducted by Brenda Milner, 1978, on temporal lobectomy patients. She found that patients with left temporal lobectomy suffered impairment in certain verbal abilities, whereas patients with right temporal lobectomy suffered from disruptions in the ability to comprehend pictures. Similarly, the right hemisphere has become strongly associated with various aspects of music perception and music production. Legiois Chauvel et al. 1998. Studies by Wilder Penfield, who stimulated parts of the neocortex during epilepsy surgery, suggested that activity in the right temporal lobe could evoke the auditory hallucinations of musical melodies. Penfield and Parrott 1963. When Rogers Sperry and Michael Gazzaniga began publishing their findings from studies of epilepsy patients in the 1960s, the idea that the two hemispheres might largely operate independently of one another gained momentum once again. Gazzaniga and Sperry 1966. Their patients had undergone a radical surgical procedure in which the corpus callosum, the fiber tract that joins the two hemispheres, was severed to prevent the spread of seizures from one side of the brain to the other. Because certain aspects of sensory processing are localized to a single hemisphere, the investigators were able to query one side of the brain independently of the other. For example, information from the left side of the visual field is represented in the right hemisphere and vice versa. Therefore, by presenting 362 and Revis Cantus and CDE stimulus only in the left or right visual field, Sperry and colleagues were able to observe how each of the hemispheres responded to it. Gazzaniga and Sperry 1966. These studies confirmed previous suspicions that the left hemisphere is much better at communicating verbally than the right hemisphere, and that the right side knows how to use and manipulate objects presented to it, even though it cannot name them. These studies led to a reevaluation of previous observations in patients with unilateral neurological insults as well as spurring new studies of such patients. In the following decades, extensive research has indicated that the right hemisphere excels in global, holistic, and intuitive processing, whereas the left hemisphere specializes in sequential and analytical tasks. In line with this view, Kaplan and Gardner, 1989, Gardner 1982, noted that when asked to draw a still life, patients with right-sided brain insults tended to produce drawings that sacrificed the gestalt for details, whereas patients with left-sided injury concentrated efforts on form and contour, rather than details. 18.5 A study of drawing in patients with dementia as a follow-up to the larger study of art production in the setting of dementia, Rankin and colleagues, 2007, conducted a study of drawing comparing 18 patients with FTD, 18 patients with AD and 15 age-matched healthy individuals. Strikingly, patients with SVPPA fared poorly on the picture completion subtest, part of the standardized Torrance test of creative thinking, TTCT, of nonverbal artistic creativity. In the picture completion subtest, participants are given a page with 10 incomplete abstract figures and asked to use the figures to draw interesting objects or pictures. They are told to make the pictures or objects as unique and unusual as possible. SVPPA patients produced drawings that were rated as more conventional and less original in content, containing fewer details and some evidence of perseverative behavior. See figure 18.2. They also produced fewer drawings overall compared with AD patients, BVFTD patients, and healthy controls. BVFTD patients showed a greater perseverative tendency to complete the incomplete figures, and patients with AD showed performance that was no different from healthy controls. Replicating these findings, another recent study also showed that patients with BVFTD are impaired on a creative thinking test compared with both healthy controls and patients with Parkinson's disease, De Souza et al. 2010. In the second part of the study, the participants were asked to draw 3 representations of common artistic subjects: a still life, which consisted of a vase holding multicolored flowers, an imagined room, and a self-portrait. When still life drawings were compared across patient groups and controls, those produced by BVFTD patients tended to show fewer details, no reference to the background, less variety, and less color. Drawings by SVPPA patients, in contrast, were richly detailed, multicolored, and often focused on a small segment of the image, such as one sprig of blue flowers, rather than on the whole. While drawings of the imagined room did not differ in number of details between groups, SVPPA patients were the least likely to include personal decorations, 38 for center, although BVFTD and AD patients also drew rooms with less personal detail. The creation of art in the setting of dementia 363 included than healthy controls, 50 for center and 53 for center respectively. Given the greater demands of this task, including internal visualization, composition, and cognitive creativity, it is not surprising that all dementia groups drew less rich, more homogeneous rooms. Perhaps the most interesting results, however, came from the self-portraits. Whereas all patient groups tended to draw more distorted and disordered images than healthy controls, BBFTD and SVPPA images were strikingly bizarre, with geometric facial features, unnatural color palettes, and disembodied heads or other body parts, seemingly floating in space. See figure 18.3. These drawings were not recognizable as portraits of the individuals who drew them, compared with those of healthy controls. Given the fact that much of contemporary art is abstract, disordered, and often bizarre, it is easy to see how the art produced by these patients might be considered more creative and critically acclaimed than the drawings produced by their healthy but non-artistic counterparts. Of course, figure 18.2 representative samples of patient responses on the picture completion subtest of the Torrance test of creative thinking, TTCT. The top panel shows 5 trials completed by a patient with SVPPA, while trials completed by AD, BBFTD patients, and a healthy control are shown below. Note that the SVPPA images are devoid of recognizable or nameable objects while the other images are clearly specific objects. Data from Rankin, Catherine P., Liu, Onlier, Howard, Sarah, Slama, Hillary, Ho, Craigie, Schuster, Karen, and Miller, Bruce L. Case-controlled study of altered visual art production in Alzheimer's and FTLD, cognitive and behavioral neurology, 21, pages 4861, doi, 10.1097/WNN.0B013E318031441DD Walters Kluwer Health. SVPPA patient, AD patient, BBFTD patient, healthy control 364 in Revivus Indus and Sozi. Although the patient's drawings might be hailed as more creative by the artistic community, the brain networks underlying art production in patients are unlikely to be the same as those used by healthy artists. Whereas artists might choose to steer away from traditional representations, patients might not be able to generate realistic images and might be less able to bring an artistic vision to life. The enhancements in creativity with a particular degenerative pattern are also often domain-specific. Skills in one domain, e.g. music, may improve creative output in that domain but may not necessarily transfer to other artistic realms. Similarly, the paradoxical facilitation of creativity with neurological disease is generally limited to a particular domain, be it gardening, painting, sculpture, music, or something else. But what is likely to be common among acclaimed healthy artists and SVPPA patients who are also artists, is perseveration or an obsession to create art. AD patient, BBFTD patient, healthy control SVPPA patients figure 18.3 self-portraits by patients in a healthy control drawn during the study published by Rankin and colleagues, 2007. Note that the drawings by patients with SVPPA show fewer personal details or characteristics, use bizarre colors and strange expressions, compared with the drawings by AD and BBFTD patients, as well as the healthy control participants. Reproduced from Rankin, Catherine P., Liu, Onlier, Howard, Sarah, Slama, Hillary, Ho, Craigie, Schuster, Aaron, and Miller, Bruce L. A case-controlled study of altered visual art production in Alzheimer's and FTLD, cognitive and behavioral neurology, 21, pages 4861, doi, 10.1097/WNN.0B013E318031441DD, C, 2007, Walters Kluwer Health. The creation of art in the setting of dementia 365 18.6 perseverative, obsessive, and visually dominated behaviors in SVPPA patients perhaps as a result of the decline in the ability to communicate and perceive the world through language. SVPPA patients tend to prefer activities that are primarily visual. Perseverative or obsessive behaviors are commonplace in patients with SVPPA. Together, both the dominance of the visual and an obsessive nature are manifest in a large proportion, 25%, of patients for whom jigsaw puzzles become the most frequent, or even the primary activity of daily living. Green and Patterson 2009. Green and Patterson, 2009, found that SVPPA patients have above-average jigsaw completion skills, especially in reality-disrupted puzzles, where expectations of the real world can interfere with puzzle completion, and in abstract jigsaw puzzles, where conceptual knowledge does not benefit performance. These patients often exhibit flat emotional affect and demeanor, but were seen to visibly enjoy the completion of jigsaw puzzles, and take pride in their skills, suggesting that an obsession can bring pleasure. This observation is encouraging both from a clinical standpoint and is a putative reason underlying the proliferation of art in this patient group. Producing art requires effort, time, and commitment, which is more easily given when the activity is experienced as fun. Inspired by this work, Espentis and colleagues, 2011, conducted a study of dementia patients, whose purpose was to investigate whether SVPPA patients might show enhanced abilities in a complex visual search task, given their tendency towards pursuing visual activities. Because the number of objects that humans are able to perceive in detail at any given time is limited, where and how attention is paid can greatly influence our experience of the world. As William James has noted, each of us literally chooses, by his way of attending to things, what sort of universe he shall appear himself to inhabit. James 1890. Therefore, by observing how and where SVPPA patients direct their visual attention, we might glimpse the processes underlying their art production. To investigate where and how visual attention is paid in our patient groups, we adapted a task pioneered by Ann Treisman and colleagues, 1980, in which participants are asked to search an array of letters for a specific target letter. Espentis et al. 2011. When the target and distractors have at least one prominent distinguishing feature, the search is conducted in parallel, that is, increasing the number of distractors has little or no effect on response time or accuracy, and the target letter seems to pop out of the display. When the features of the target and distractors overlap, however, the search is conducted by investigating each item one at a time, causing the response time to increase with the number of items in the array. During the serial search, participants are more likely to make errors as the number of distractors increases and or the time to complete each trial is limited. Treisman and Gillard 1980. Because we were primarily interested in where and how visual attention is paid in patient groups, we monitored participants' eye movements, in addition to recording accuracy and response times. Finally, to understand the brain basis of this behavior, we used a technique called voxel-based morphometry 366 and Revivus Indus and Sozi (VBM) that quantified differences in brain volume that correlate with performance on the task. We found that as their performance on the jigsaw puzzle task suggested, SVPPA patients did, in fact, show enhanced performance on the most difficult visual search task. They were notably faster than healthy controls during the serial search trials with the largest number of distractors. These patients were just as accurate as healthy controls during both pop-out and serial search. AD patients, in contrast, showed significant impairments even under the easiest conditions, and their performance was no different than chance during the most difficult serial search trials. BBFTD patients were significantly worse than controls only under the most difficult serial search conditions, and, like controls, their response times increased with the number of distractors in serial search. Strikingly, SVPPA patients showed no increase in response time when the display size was doubled from 15 to 30 items in the serial search condition, and found the target more quickly than all other groups even while looking at a smaller proportion of the image. See figure 18.4. We interpreted these findings as suggestive of the fact that SVPPA patients may have a more efficient visual search strategy that allows them to ignore distractors and find the target more quickly than healthy people. Next, we were interested in determining which brain regions were associated with better performance on this task. To that end, we conducted a VBM analysis which demonstrated that better serial search performance correlated with gray matter volume in a bilateral dorsal frontoparietal network across all participants, including a region in the superior parietal lobe, the precuneus, the middle frontal gyrus, and higher visual regions in the occipital lobe. This network is known to support visual attention and is spared in patients with SVPPA. Because the serial search task relies heavily on the process of integrating separate visual features into one coherent image, it is not surprising that the region of the parietal lobe that correlated with better performance in this task has also been shown to result in visual binding problems when it is damaged, as is the case in patients with Fallings syndrome or hemispatial neglect. Damasio 1985. On the other end of the spectrum, hyperactive binding, or the melding of information from different sensory association areas as is seen in individuals with synesthesia, has been correlated with neural activity and more gray matter in the parietal lobe. Weiss and Fink 2009, and greater inferior connectivity in a region of the parietal lobe that nearly overlaps with the part of the superior parietal lobe shown to correlate with better performance on our task. Raw and Schulte 2007. In our study, we found no significant differences in gray matter volume in the superior parietal region between patients with SVPPA and their healthy counterparts. This observation implies that the enhanced visual search function in our SVPPA patients might reflect a change in functional rather than structural brain differences. In summary, the results of this comprehensive study of visual search in people with SVPPA suggest that the paradoxical enhancement of visual artistry seen in certain patients might reflect a shift in attentional space from language division, which may reflect changes in connectivity in the dorsal parietal network. The C ratio NOFR die in the SETI NGOF dementia 367 proportion of time healthy controls 0.08 0.06 0.04 0.020 0.08 0.06 0.04 0.020 0.08 0.06 0.04 0.020 0.08 0.06 0.04 0.020 SVPPA BBF TDAD figure 18.4 examples of visual search patterns during conjunction search. Representative plots of eye movements during a conjunction search trial with a display size of 30 items. Target is indicated by the arrows in the NC figures. The top panel shows a histogram of the proportion of time spent in each part of the figure, with a density map, smooth Gaussian distribution, of the same data shown below. The data shown here are representative of 10-14 trials in each patient group. Reprinted from Neuropsychology, 49, 3, and Ravi Viscontas, Adam L. Boxer, John Fizenko, Elisa Matlin, Hilary W. Brewer, Jacob Mirsky, and Bruce L. Miller. Visual search patterns in semantic dementia show paradoxical facilitation of finding processes. Pages 468-78, copyright, 2011, with permission from Elsevier. 368 and Ravi Viscontas and Soci 18.7 a comprehensive case study after the initial discovery by Miller and colleagues, 1998, of patients whose artistic talents emerge or proliferate after disease onset. One case in particular stood out as exceptional. Sealy ETAL 2008. Ann Adams was a cell biologist until, at age 46, her son was in a serious motor vehicle accident. She took a leave of absence from her academic career to care for him and, around the same time, began to paint. Once her son recovered, she decided not to return to academic life and spent more and more of her time in her studio. Although she had a lifelong interest in art and music, her earlier paintings were primarily simple drawings and architectural watercolors, characterized by muted color schemes and classical perspective. Between ages 46 and 52, however, as she was spending more and more time painting, her work became much more vibrant, colorful, and multifaceted. She synthesized her love of music with her artistic output by painting representations of favorite musical pieces. At the same time, she began to show an increased tendency to pun, which was also reflected in her artistic choices. When she was 53, she began to paint what would become one of her signature masterpieces, Unraveling Bolero, an homage to Maurice Ravel's most famous piece. She laid out the music, measure by measure, into an intricate, exacting, and compulsively detailed diptych, which took her 4 years to complete. Oddly, Maurice Ravel, 1875-1937, himself suffered from a progressive aphasia, and composed his Bolero in the early stages of his disease, at age 53. The piece is a study of perseverations, Amadou ETAL 2002, with the reiteration of a simple melodic theme, accompanied by a simple, incessantly repetitive bass line. Despite the fact that it became his best known work, Ravel himself considered the Bolero a rather trivial opus, describing it simply as a piece for orchestra without music. He explains, I'm going to try and repeat the theme a number of times without any development, gradually increasing the orchestra as best I can. Orenstein 1991. After writing Bolero, Ravel's illness gradually progressed until he died 8 years later. Unaware of Ravel's illness, Ann Adams painted her Bolero, in a precise and compulsive fashion, with the height of each of her rows signifying the increasing texture and volume of the orchestra. After Bolero, the subject of her paintings shifted from music to even more abstract concepts such as height, and a series of paintings of invertebrates arranged as letters that together created a complete alphabet. Shortly after her completed Bolero, her language symptoms, harbingers of NFVPPA, were first noticed. Initially, as her language declined and she showed no other cognitive impairments, she turned towards photographic realism and her paintings became vividly realistic and intricately detailed. By age 64, she was nearly mute. In NVFPPA, atrophy begins in the left frontoauricular cortex, leaving patients with effortful, non-fluent speech, cornotempony ETAL 2004, and difficulties with grammar and articulation. In Ann Adams' case, structural and functional imaging demonstrated enhanced gray matter inactivation in heteromodal associative, IPS/SPL, and polymodal, STS, neocortex in the right hemisphere, Sealy ETAL 2008. These areas are involved in the creation of art in the setting of dementia 369 visual motor search and attentional control, Corbetta and Schulman 2002, Sealy ETAL 2007, and sensory transcoding, necessary for sight reading music, Surgeon 1992, Sean ETAL 2002. These regions are also part of the same network that seems to underlie enhanced performance on the serial visual search task described above. BBM has also demonstrated enhancement in these same regions in professional musicians, Gazer and Schwab 2003. Taken together, these studies point to the possibility that as one brain region degenerates and loses functionality, another region might be gaining functionality and even gray matter volume as a result of changes in behavior and/or compensatory activities. Then the question becomes one of the chicken or the egg. Does the creative impulse lead to the behavior, which causes rewiring over time? Or, does rewiring occur as a result of degeneration elsewhere, leading to changes in behavior? Assuredly, the answer is likely both. 18.8 Theory of creativity in patients with dementia, release of inhibition despite its popularity. The idea that creative thought is restricted to the right hemisphere while scientific or logical thought is restricted to the left hemisphere is patently false. If this supposition was true, then one would find many examples of people with neurological damage to the right hemisphere with no loss of rational or logical thought, and people with left hemisphere damage with no loss of creativity. No scientist would ever argue that science does not involve creativity, and no artist would contend that art does not demand rigorous analysis or meticulous attention to detail. Furthermore, even the neurologist Joseph Bogan, who participated in early studies of split-brain patients and was an active promoter of the hemispheric asymmetry perspective, conceded that the neural basis of creativity resulted from the functional specialization of the two hemispheres and the combinatorial interaction of the hemispheres which requires the corpus callosum. Bogan and Bogan 1988. Both hemispheres are involved in different aspects of creative cognition. However, an insult or degeneration localized to or disproportionately affecting one hemisphere or the other can have profound effects on a person's perceptions and focus, altering creative thinking and execution. There is some evidence that in the context of focal cerebral infarctions, regional blood flow to unaffected areas can be greater than in healthy control participants. Weiler ETAL 1992. Not surprisingly, the pattern of functional reorganization as the patient recovers does not seem to follow a universal map, but differs between individuals. Weiler ETAL 1993. Miller and colleagues, 2000, suggested that the paradoxical emergence of visual artistic talent in patients with predominantly left-sided anterior temporal lobe degeneration, as is the case in patients with SVPPA, might reflect a release from inhibition of the more right-sided posterior and dorsolateral frontal regions involved in visual art production and creativity. Miller and colleagues, 1998, also proposed that the accompanying deficits in social and other cognitive functioning that the patients experience may have led to the facilitation of artistic skills through the release from inhibition of these skills. Wilder planning, 370 and Ravi Viscontas and Soci organization and motivation, processes relying on intact frontal regions, remained intact, and they were able to access fairly remote memories from which they produce realistic reproductions of visual images. They showed marked deficits in semantic memory and verbal prowess. As a case in point, Mel, Howard, and Miller, 2003, described an accomplished visual artist who developed FTD. At the age of 49, this woman began to develop her own unique painting technique, producing complicated patterns with Chinese horoscope icons. This development coincided with the onset of illness and a progressive decline in her ability to perform her duties as a high school teacher. Decline in language function coincided with enhanced creativity in her paintings. They grew more emotionally intense and impressionistic, and less realistic and detailed. Similarly, Kaczmarek, 1991, described a painter who suffered a left hemisphere stroke that resulted in aphasia. Unlike the woman described above, this painter retained the ability to draw realistic pictures. In contrast, the painter lost the ability to create the highly symbolic pictures that characterized the paintings that he had completed before his stroke. The idea that creativity stems from the release of baseline inhibitory activity is at the heart of another prominent theory of creative cognition. This theory has been championed and studied most thoroughly by Colin Martindale, but also has a long history as reflected in the 19th century notions regarding the relationship between degeneration and psychoticism advocated by Morel as far back as 1857. Supporting this notion is the observation that atrophy of higher inhibitory centers of the brain resulted in a constellation of symptoms such as criminality and over-emotionality, traits that overlap considerably with those used to describe eccentric, highly creative individuals. Martindale's theory emphasizes cognitive disinhibition, or the ability to shift schematic constraints and biases that impede creative thoughts and/or actions. Martindale 1999, Martindale 1971. In the context of this theory, degeneration in the dominant hemisphere, as seen in SVPPA patients, might result in greater functional activity and rewiring between posterior visual areas and prefrontal cortex over time, such that previously untapped creative potential emerges in the setting of disease. 18.9 Conclusion and future directions. Although neurodegenerative diseases cause profound loss of memory, personality, and other aspects of thinking, the emergence of visual artistic abilities provides a window into understanding brain networks that serve visual creativity. A long history of studies and theories regarding left versus right brain functional specialization frames an understanding of how patients with neurodegenerative disease asymmetrically affecting one brain hemisphere may develop prolific visual artistic ability. With the advent of technologies such as functional MRI, scientists have been equipped to parse visual perception into tractable components, revealing possible mechanisms underlying the neural basis of visual perception and creativity. Neuroscientists will probe further into how brain networks for various functions work in concert with each other. It may be that specific brain networks take center stage as the functional demands of the human change from moment the creation of art in the setting of dementia 371 to moment. Understanding these relationships will shed light on whether the release of inhibition as a theory for the emergence of visual creativity in patients with neurodegenerative disease holds true. 19.1 Introduction. Hemispheric specialization is a hallmark of human cognition when compared to all other animals. It describes the fact that the left and right cerebral hemispheres separately control different functions of the mind. Corvallis 2009. For this reason, functional brain lateralization is a source of much scientific curiosity and research. The notion of functional lateralization for art, in particular, gained a solid foothold in neurological and neuroscientific thinking in the 1960s and 1970s following the dramatic findings of the commissurotomy cases in Roger Sperry's lab at Caltech, Sperry 1974, Trevarden 1990, Zagel 1993. These studies were particularly suited to the discovery of which cognitive functions are specialized in one or the other hemisphere, and this explains the excitement surrounding the findings. Before that time, the nature of hemispheric specialization was not adequately characterized, even though functional cognitive asymmetry was long understood to be a unique feature of the human brain. By now, countless empirical findings, conducted with both normal subjects and brain-damaged patients, have supported the notion that the left and right hemispheres have separate cognitive and thinking styles. Corvallis 2012, Springer and Deutsch 2001. The left hemisphere specializes in the main language functions, detail, and focused cognition, and applies logical, deductive thinking styles. The right specializes in visuospatial functions, including topographical knowledge, face perception, and memory, and holistic, global, and gestalt thinking styles. The asymmetrical hemispheric specializations are now viewed as complementary to each other and controlled by interhemispheric dynamics shaped by adaptive evolution. Sperry 1974, 1981. Despite the specialization, in the normal brain, the two cerebral hemispheres work in tandem. This is what enables humans, more than any other biological organism, to communicate with others through a sophisticated combinatorial language as well as through art, to navigate expertly in their environment, to build lasting constructions, to create, and to innovate. At the time when the increased interest in art and its functional brain lateralization was sparked, art was art. It was lumped into a single unitary entity. The myriad of art types were not elaborated upon. Paintings and drawings received the greatest attention as instances of art. There was no meaningful discussion of the brain of the artist as distinguished 374 W. Zagel from that of the viewer of the art. The components of art were not fractionated with respect to their possible neurological components, and, importantly, the lateralization notions for art were applied exclusively to right hemisphere specialization. What was emphasized outside Sperry's laboratory, by scholars and non-scholars alike, was that art by its very nature is antagonistic to language and must be supported by a non-language system in the brain, namely the system specialized in the right hemisphere. Zagel 2013. However, this was an inference, not a scientific fact. No empirical studies directly measuring aspects of art were published by the Sperry laboratory, nor were any of the commissurotomy patients professional artists. But, sadly, this association between art and hemispheric specialization has since dominated interpretations of scientific data dealing with art and brain, by both scientists and laypersons alike. This chapter reviews the background as well as discusses findings on brain laterality in art. 19.2 Historical background for hemispheric lateralization in art is noted above. The association between hemispheric specialization and art was jump-started by the work on the complete commissurotomy patients of neurosurgeons Bogan and Vogel who were studied in Roger Sperry's psychobiology laboratory at Caltech in Pasadena, California. Bogan and Vogel 1962, Sperry 1968, 1981. These patients underwent surgical midline disconnection of fibers in the forebrain commissures, namely, in the corpus callosum, anterior, and hippocampal commissures in order to relieve severe, intractable epilepsy that no longer responded to medication. Following surgery, they were tested and studied in Sperry's laboratory because the surgical disconnection allowed, for the first time, direct assessment of hemispheric competence. This was a greatly improved and reliable method for determining hemispheric specialization. Moreover, previously held certainties about the right hemisphere, mostly derived from the study of patients with unilateral focal damage, were challenged through empirical tests and shown to be wrong in that more abilities were controlled by the disconnected right hemisphere than was thought to be the case. Sperry 1981. Prior to the galvanizing effects of the studies with the complete commissurotomy patients, the scientific findings on groups of neurological brain damaged patients, where the damage was unilateral and focal, provided initial evidence for functional brain asymmetries. Those results were known and discussed in the confines of neurology and neurosurgery. The lateralization of the language brain areas to the left hemisphere after the mid-1800s, notably by Paul Broca and Carl Wernicke, inspired countless of functional localization observations in the brain. The preferred strategy was, as noted earlier, the study of neurological patients with unilateral damage confined to a single hemisphere. If patients were unable to carry out a particular task after the damage, which they were able to do beforehand, the damaged area was inferred to control, was responsible for, that function in the intact brain. However, with the complete commissurotomy patients in Sperry's laboratory, direct testing of hemispheric competence as opposed to negatively inferring competence from brain damage, as is done in the case of focal, unilateral damage, became hemispheric specialization, art, and aesthetics 375 possible. Consequently, there was much enthusiasm in scientific circles for results and ideas emerging from Sperry's laboratory, so much so that assumptions and inferences were made about hemispheric specialization, particularly that of the right, without empirical evidence upon which to base them. In general, one major reason art and brain had remained an enigma for so long, despite the classic 1948 publication by Lachwani on a few artists with brain damage, Lachwani 1948, Gardner 1975, 1982, is that precious few talented individuals in society are capable of producing art, and of those, very few come to the attention of neurologists. From a neurological perspective, pairing art with its neuroanatomical underpinnings would not have universal application, whereas agnosia, loss of previous knowledge about specific things, apraxia, loss of voluntary purposeful movements, or aphasia, acquired language impairments, would apply universally. Consequently, most neurological, neuropsychological, and neuroscience laboratories devoted efforts into elucidating those conditions, leaving brain control of art as esoteric and mysterious issues. Only in the past 15 to 20 years or so, with the advent of neuroimaging techniques, have we seen a growth in the study of the neural underpinning of art, albeit mostly in visual and the musical arts. Zagel 2005, Nadal 2013. 19.3 The right hemisphere in art. Several factors in scientific and intellectual thinking contributed to the notion that art is an expression that can be lateralized in the brain. The lateralization applied specifically to the right hemisphere. The most significant of the factors concerned the nonverbal nature of right hemisphere cognition and its specialization in visuospatial cognition. In neuropsychology and neurology, investigating left hemisphere cognition has been a straightforward endeavor, because the main language centers are represented in the left, and failures in language communication are relatively easy to detect and measure. The right hemisphere, by contrast, has been an enigma and a challenge to researchers because it lacks language's communication channels. The publications from this very laboratory pursue the mystery of the right hemisphere by attempting to understand its functions and cognitive style. Consequently, several empirical facts and reasonable conclusions emerged. Right hemisphere cognition, A, is indeed, for the most part, nonverbal in nature, B, specializes in visuospatial tasks, and C, in holistic, gestalt thinking styles. Against this background, conceptual characterization of what other functions might be specialized in the right hemisphere has led to inferences noted earlier that ended up guiding data interpretation, namely that the right hemisphere is A, artistic, because visuospatial abilities were assumed to be the very essence of art, B, emotional, because emotions are nonverbal, and C, creative, because, again, creativity is nonverbal. But they were mere conjectures, born out of speculation, and they lacked empirical support. At the heart of the logic was the nonverbal aspect of right hemisphere cognition together with the nonverbal nature of visual art, as well as of emotions and creativity. It was assumed then, and now, based on personal subjective observations, that 376 W. Zagel thoughts, ideas, emotions, and creativity reflect a neural source lacking language, and thus must be formed in the right hemisphere. Subjectively, they appear languageless. In fact, we do not know how all of these are formed and cannot be certain that they do not arise in the left hemisphere. The ensuing decades did not support these notions about the lateralization of art to the right hemisphere. Indeed, they may be viewed as derailing research into brain, art, and creativity. Researchers were swayed by fashionable notions and felt they had to interpret their empirical findings in light of those unsubstantiated conjectures, while being largely unaware of what gave rise to them in the first place. In reality, there was no evidence that Sperry's artistically unskilled complete commissurotomy patients sketched or made drawings of superior quality when using the left hand, controlled by the right hemisphere. They did, however, copy two-dimensional representations of three-dimensional figures, such as a cube, better with the left than with the right hand. This was in agreement with neurological patients with damage in the right hemisphere, particularly in the parietal lobe, who could not, on the whole, accurately copy a cube or any other pictorial representations. Bogan 1992. This type of performance contributed to the conclusion that the normal right hemisphere specializes in visuospatial perception. However, because art was viewed as the conglomerate art, irrespective of whether or not it was pictorial, musical, literary, and so on, the realization that spatial ability is not key to artistic expression was not reached. Even one of the important researchers into brain and art, Howard Gardner, was influenced by the general findings about the commissurotomy patients in Sperry's laboratory. Gardner 1975, 1982. Fashion in science exerts powerful influence on scientific opinions and data interpretation. 19.4 Perceptual effects of right hemisphere damage in artists. Damage in the right hemisphere, in artists and non-artists alike, results in commonly observable deficits in perception, and this leads to alterations in the way they depict their art. Most of what we know is based on visual art, most of it pictorial. It is not as if the damage has led to changes in artistic expression for SE, rather, the alterations reflect the inability of the brain to process visual information in a complete way. In other words, observable alterations reflect broken perception, and the perceptual processes themselves do not define artistic talent, creativity, and expression. One example of a perceptual deficit following brain damage is hemineglect of the left half of space, whether the space is personal, on and around the person's body, or extra-personal, away from the person's body. With artists, the neglect manifests in leaving out details in the left half of the canvas. For example, some of the well-known artists who displayed such effects in their works following right hemisphere damage are Anton Rederscheit, Otto Dix, and Lovis Corin. See Boguslavski and Bowler 2005, Zabel 2005. It would seem that a central invisible midline axis divides space into left or right, and the half that is ignored is typically left of the midline. The symptoms consist of failing to attend, orient, draw, paint, eat, comb, and so on in the patient's left space. The damage is typically hemispheric specialization, art, and aesthetics 377 in the right parietal lobe, although damage in the thalamus or even subcortical areas in the right hemisphere can give rise to hemineglect. The prevalent interpretation for the hemineglect is an imbalance in hemispheric control of space such that the left hemisphere becomes abnormally dominant in grabbing attentional resources to the right half of space. Heilman et al. 2000. In most patients, the neglect symptoms dissipate in 6 to 8 weeks and this contributes to the proposal of an imbalance, albeit a temporary one. It is important to emphasize that the effects are observed in most of the cases only in the left half of space, that they have right hemisphere damage, and that the effects apply to both artists and non-artists alike. Thus, the perceptual alterations observed in the artist's works are not restricted to how the brain controls the production of pictorial art. Another outcome of right hemisphere damage, particularly when it is localized in the parietal lobe, is spatial perception disturbances such as spatial agnosia and topographical agnosia. In the former, the understanding of relationships among objects or among abstract geometrical lines is lost. In the latter, knowledge of previously known routes, maps, layouts, and so on is no longer accessible. The whole notion that the right hemisphere specializes in visuospatial perception and knowledge originated with observations of patients suffering from such damage. In addition, when the damage is localized in the fusiform region, roughly the inferior junction of the occipital and temporal lobes, it leads to severe disturbance in recognizing previously known faces, a condition known as prosopagnosia. The condition also impairs recognition of newly encountered faces. When considering the effects of left or right hemisphere damage in more than 50 brain damaged artists, several conclusions emerged. Zagel 2005. The first is that neither unilateral hemispheric damage leads to specific, characteristic alterations in art. The second is that any alterations that do emerge post-damage, alterations do not always emerge, are not unique to art, they merely reflect perceptual deficits of the kind observed in non-artists as well. The third is that the only aspect of an artist's work that seems to change following the damage is the technique, not the skill or the talent. Due to acquired motoric problems, artists suggest their artistic expression with different techniques. 19.5 Perception of paintings in the left and right hemispheres. Most studies on art and brain assume that the artist's production and the viewer's observation are one and the same. They are not. To learn the underlying neural mechanisms of the production we need to look to the artist, while to learn the neural underpinning in the observer we need to study the observer. The former aspect can be determined through the study of professional artists with unilateral focal brain damage, discussed in subsequent sections of this chapter. The latter can be studied through the use of the hemifield technique in normal subjects. The first study to put to a direct test the question of right hemisphere superiority in art perception was a hemifield study in normal subjects, Zagel and Kosher 1989. It investigated hemispheric differences in the perception of surrealistic versus realistic paintings. Subjects viewed the pictures of a series of 24 paintings, 378 W. Zagel, 12 surrealistic and 12 realistic, in the center of vision, and then had their recognition memory of the paintings tested in a hemifield paradigm. In this recognition phase, a total of 48 pictures, of which 24 were the original to be remembered pictures and 24 were decoys, half were surrealistic and half realistic, were projected briefly, 100 milliseconds, in the left or right visual half fields. They pressed a key to indicate yes, they remembered seeing the painting in the to be remembered series, and a no key to indicate they had not seen the painting in the memory series. The The results showed superior memory for the surrealistic paintings in the right visual half-field, left hemisphere, and no difference between the left and right visual half-fields for the realistic paintings. The above hemifield study indicated not only absence of right hemisphere superiority in remembering paintings, but also that not all paintings are the same. The surrealistic paintings depicted the world through violations of reality rules, some representing logical violations, while some representing physical violations, and this particular type of reality distortions favors left hemisphere cognitive processing. The content itself influences the hemispheric role in processing the painting. When it comes to realistic depictions of the known physical world, it seems both hemispheres have equal cognitive approaches. Other painting genres were not tested, unfortunately, or that may have provided a continuum on which to determine hemispheric asymmetry. Similarly, in a different study, pictures generated by a computer to depict abstract style paintings and realistic style paintings were applied in a hemifield paradigm to normal subjects, both in Magnus in 2005. Some of the subjects were professional painters and some were laypersons. All subjects were asked to remember the pictures. The results revealed that the abstract pictures were better remembered in the right hemisphere. The pictures depicting the realistic style were remembered better by the artists in the left hemisphere, and in the right hemisphere by the non-artists. These results support the notion that art is not a single entity. Rather, that art can be fractionated into separate different genres, and how viewers process the art depends on their expertise. Thus, again, the idea that a single hemisphere, the right, can specialize in art is untenable. 19.6 Drawings in the right hemisphere. What is known about the right hemisphere in drawings? Neuropsychologists in Britain asked their brain-damaged patients to draw a bicycle from memory. The damage was in the right or left parietal and occipital lobes. The drawings had characteristic errors. The right brain-damaged group omitted the contour frame but left in the details of the bicycle parts. The left brain-damaged group drew the contour frame and omitted the bicycle parts details. McPhee and Zangwill 1960, Patterson and Zangwill 1944, Warrington and James 1966. The damage in the right hemisphere abolished the ability to depict the gestalt, whole, global bicycle configuration, and the damage in the left hemisphere abolished the ability to depict the details and pieces of the bicycle. These findings prompted Patterson and Zangwill, 1944, to propose that the right hemisphere uses a cognitive strategy heavily dependent on global and gestalt configurations, while hemispheric specialization, art, and aesthetics 379 the left applies a strategy that emphasizes local details. However, with regards to drawing and the brain, by non-professionals, these findings show that neither hemisphere alone controls drawing abilities. Subsequently, Kurt and Kurdish, 1993, asked 125 patients with unilateral, focal brain damage to draw 7 figures from memory: cube, circle, square, clock, tree, house, a person. The patients with right hemisphere damage displayed spatial relations errors, and those with the left damage had numerous errors of various kinds. The key finding is that the ability to draw was not abolished in either group. Thus, we can assume that in the normal brain, the control of drawing is present in each hemisphere. 19.7 Lateralized and bilateral brain activation with EEG and fMRI laterality effects have been tested mainly in non-artists. They have been reported in both electroencephalography, EEG, and functional magnetic resonance imaging, fMRI, studies, but those effects were not limited exclusively to a single hemisphere. Neurophysiological responses such as EEG uncovered some lateralized effects in viewing paintings. Hoefel and Jacobson, 2007, recorded evoked potentials from surface skull electrodes in normal subjects while they were making aesthetic judgments of graphic patterns. They found pronounced right hemisphere lateralization in late positive potentials, particularly 600 milliseconds after the initial exposure of the graphic pattern. On the other hand, fMRI studies in which subjects made aesthetic judgments of paintings revealed a predominant left hemisphere activation as follows. 1. Jacobson and colleagues, Jacobson et al. 2006, found maximal bilateral activation of the inferior frontal lobe gyrus, Brodmann areas 45 and 47, lateralized increased activation of the left lateral orbitofrontal region, in the left temporal pole region, as well as in the temporoparietal junction region. They also reported activation of the right Brodmann area 10, frontal lobe, as well as the right posterior cingulate gyrus. 2. The fMRI work of Kupchak and colleagues, Kupchak et al. 2009, revealed bilateral maximal activation of the insula, Brodmann area 13, during aesthetic judgments in the left lateral prefrontal cortex, Brodmann area 10, the left superior parietal lobe, left cingulate, Brodmann areas 24 and 32, and left lingual gyrus region, Brodmann area 19. Similarly, Ishizu and Ziki, 2011, explored explicit aesthetic reactions to pictures of paintings and measured responses to how beautiful they were on a 9-point scale. They found numerous hemispheric regions that were maximally activated in judgments of beautiful. They were in the left medial orbitofrontal cortex, left caudate nucleus, and left inferior occipital gyrus. For judgments of ugly, they found maximal bilateral activation of the amygdala as well as the left postcentral gyrus, somatosensory cortex. Bessel and colleagues, Bessel et al. 2012, found maximal activation in the left hemisphere, specifically in the anterior medial prefrontal cortex, hippocampus, substantia nigra, and posterior cingulate gyrus. They found a large area of activation in the medial area of the left hemisphere, including the thalamus. Barely any activation in the right hemisphere was noted. 380 WZAL reviews of fMRI results in studies measuring subjects' responses to pictorial material have been reported. Nadal 2013, Nadal et al. 2008. Together, these results support the notion that art evaluation lacks a consistent lateralized localization in the brain. 19.8 Painted portraits. Lateralization of the face in art and viewers' aesthetic reactions for hundreds of years, particularly since the Renaissance. Western artists have painted single sitters with a lateralized pose. Previously, profile views of faces were the norm. From the Renaissance onward, they showed more of the left side of the face than of the right, and this was especially true for women's faces, more so than for men's. McManus and Humphrey 1973. McManus and Humphrey found that more women than men sitters were painted so that the left side of the face was more exposed, 68% versus 56% respectively. On the surface, there was no reason why artists would show such bias in their works. The background for this outcome is described by Zadel, 2005. Thus, an empirical attempt to understand the basis for the side bias in Western portraiture was launched many years after those results were first published. Zadel and Fitzgerald 1994. The first key conjecture was that the principal determinant in the bias was a preference by the observer, particularly the paying observer. For hundreds of years, artists made a living through commissioned portraits. The working hypothesis was that observers liked to view women's left side of the face more than the right, and that artists wanted to accommodate them. They wanted their works to be liked. They spent days, weeks, months, and even years on a given portrait, e.g. Leonardo's Mona Lisa. The bias could not have been some random and haphazard event. Thus, it was important to find out what subjects think by way of liking a portrait. Subjects in a laboratory were shown painted portraits of single sitters and asked to judge on a 5-point scale the degree to which they liked the painting as a whole. A separate group of subjects were shown these portraits and asked to judge them on a 5-point scale according to how attractive they considered the sitter. In each type of judgment requirement, one group of subjects saw the original orientation of the paintings and another group saw a mirror reversal version of the paintings. The unexpected findings were that in each type of judgment, regardless of whether the original orientation or its lateral reversal were shown, women sitters whom the artist originally painted with the right side emphasis were preferred. The painting was preferred as a whole and the sitter was considered much more attractive than paintings where the left side was emphasized. Moreover, no significant left emphasis versus right emphasis was found for the men sitters, in each type of judgment. One would have expected at the very least that portraits of women with left side emphasis to be the most preferred, since this is the Western trend in painted portraits. However, the fact that gender difference emerged in the portrait phase indicated that the subjects picked up, unconsciously, an artistic bias after all. There was no statistically significant sex difference in the judging subjects. Zadel 2005, pages 166-7. These results indicate that artists' bias in depicting faces is more a reflection of their own aesthetic, perceptual, and cognitive preference than that of naive observers. To test whether or not facial attractiveness is organized asymmetrically on human faces, another experiment in which head-on photographs of people's faces were used to determine attractiveness preference was carried out. After digitizing the photographs, which were taken with hemispheric specialization, art, and aesthetics 381 straight-on views with neutral expressions, each photograph was made into a left face and a right face with the aid of Adobe Photoshop. Chen ETAL 1997, Dale ETAL 1995. When subjects were shown these perfectly symmetrical left and right faces and asked to decide which one is the most attractive, they chose the right for women's faces and revealed no significant difference between the two for men's faces. These results illustrate the difference between the artist's artistic decision and the viewer's artistic preference. Thus, when it comes to aesthetic judgment, we need to distinguish between the brain of the artist, who is the producer of the art, and the viewer's brain. 19.9 Conclusion. The emphasis in brain and art research thus far has been on pictorial art. With this in mind, the behavioral data, physiological brain recordings, functional imaging techniques, measured in the observers of the art, as well as effects of unilateral brain damage in professional artists, together point to an absence of hemispheric specialization for art. Instead, the collective data indicate that art is not a unitary entity, that multiple art-related components are involved in producing it. Some are features of the producing artist's brain, some are features of the expressive medium of art, e.g. pictorial, musical, literary, dance, and some are features of the observer's brain. From a purely logical point of view, it is not reasonable to assume that there is a hemispheric specialization for producing and observing art. It is more parsimonious to assume that subcomponents of art are specialized in different hemispheres and that both hemispheres contribute to the final product. Chapter 20 Towards a Comparative Approach to Empirical Aesthetics. Jesha Westphal Fitch and W. Tecumseh Fitch 20.1 Introduction. Aesthetic traditions are ubiquitous in human societies and seem to be a human cultural universal, akin to language and music. Empirical aesthetics is emerging as an area of cognitive research on a PAR with musicology and linguistics and its potential to reveal fundamental properties of the human mind. Empirical aesthetics, as we understand it, focuses on the processes underlying the interaction of one or more individuals with an aesthetic stimulus, often visual, during both perception and production of the object. An important aim of this research should be to describe and understand the worldwide human drive to create and surround ourselves with objects that are pleasing to one or more of the senses, in a way that goes beyond their immediate utilitarian function. There is a rich potential for comparative work in aesthetics. First, differentiating cultural specific features from universally shared elements necessitates studying aesthetic traditions across a wide range of human cultures. This is analogous to searching for and defining universal features present in all languages, e.g. different word classes such as verbs and nouns, versus language-specific features, such as the Chinese tonal system. In addition to cross-cultural comparisons across species are required to distinguish those components of the aesthetic process that are uniquely human from those shared with other species and to discover possible examples of convergent evolution. In this chapter, we consider some common features of human aesthetic traditions with a particular emphasis on early artifacts incorporating non-representational patterns, and we discuss their possible evolutionary origins. Non-representational patterns and ornaments are present in most, if not all, human cultures. However, they are not a typical research focus in empirical aesthetics, where the main focus has been on Western high art. From a cross-cultural view, however, it makes sense to study abstract ornamental patterns due to their ubiquity and relative simplicity. Cf. Westphal Fitch ETAL 2012, Westphal Fitch ETAL 2013. We therefore emphasize the importance of geometrical and non-representational patterns here. Biologically, it seems likely that many low-level perceptual components of the aesthetic process are shared with other species, while certain aspects, e.g. production of repeated hierarchically organized patterns, may well be unique to our own. Such features may also 386 Jesha Westphal Fitch and W. Tecumseh Fitch be present in other human domains such as music or language, with important implications for our understanding of the nature of the human mind. In this chapter, we review literature on symmetry perception and on nest building in birds, bees, and primates, two areas where we think known similarities and differences between humans and animals concerning aesthetics can be usefully pursued. It is vital to study not only chimpanzees and other primates, Zadel ETAL 2013, but also species that may have evolved traits convergently, for example birds. In particular, we highlight the need to take the ecology and sociobiology of a species into account in order to understand the mechanisms by which pre-existing traits can become exaggerated and gain social importance beyond their immediate function. 20.2 Pervasive issues in aesthetic inquiry. We begin with a short discussion of the historical development of aesthetics, observing that the sharp distinction between ornament and high art is a relatively new phenomenon idiosyncratic to Western European cultures. We also consider attention at the heart of all aesthetic inquiry, namely that between the broad pan-human universality of aesthetic activity and the wide variety of superficial fashions and traditions that may change rapidly in individual cultures in time periods. 20.2.1 Natural and acquired aesthetics. Beyond Kant, although aesthetics began as a purely philosophical discipline, with the advent of Gustav Fechner's writings introducing an empirical approach to aesthetics, Fechner 1871, 1876, scientists began to gather data on aesthetic behaviors. This makes empirical aesthetics one of the oldest branches of psychology, dating back to the 1870s. Our modern Western conception of the fine arts as high art phenomena, distinct from ornament and craft, is a relatively new one which emerged in 18th century Europe, Crisolo 1990, Shiner 2001. Prior to that, and hence for the vast majority of human history, no strict distinction was made between art and craft, and in many cultures this distinction does not exist. Anderson 1979. The concept of aesthetics as a distinctive kind of appreciation specific to art, as opposed to good taste which might apply to any number of things, arose at roughly the same time in Europe. The word aesthetics derives from the Greek aesthetico, meaning sentient or sensory, cf. the medical term anesthetic. Aesthetics was first used as a term to describe appreciation of beauty in 1750 by Alexander Baumgarten, Gregor 1983, Shiner 2001. Baumgarten proposed aesthetics as a second cognitive mode that relied on the senses, cognitio sensitiva, in addition to rational thought. In his model, rational thought is independent of sensory input, but cognitio sensitiva relies mainly on input through the senses. Additionally, Baumgartner differentiates between the natural and artificial, acquired, aesthetic sense. While humans are born with a natural aesthetic sense, Baumgarten calls it a natural disposition of the soul for beautiful thought, dispositio naturalis animi ad pulchre cogitandum, Gross 2001, p97. Enculturation leads to a refinement of this sense. Towards a comparative approach to empirical aesthetics 387 we interpret this natural aesthetic sense that Baumgarten describes as the aesthetic sense that is shared between all humans, regardless of cultural surroundings, while traits specific to a culture are acquired in a later enculturation process, or refinement, in Baumgarten's terms, during ontogeny. Beauty for Baumgarten is a cognitive phenomenon and an aesthetically minded perceiver. Beauty is perfect perception, and not a property of the object being viewed. Gross 2001. This is reminiscent of David Hume's famous statement, Hume 1757 beauty is no quality in things themselves. It exists merely in the mind that contemplates them, and each mind perceives a different beauty. Baumgarten's original concept of aesthetics crucially attributes the capacity for aesthetic perception to all humans, with the proviso that enculturation can refine this ubiquitous natural aesthetic sense. This contrasts sharply with the very influential concept of aesthetics proposed by Immanuel Kant, presented in Critic der Welscraft, Critique of Judgment, Kant 1872. The key concept for Kant is disinterested contemplation. Kant posits that a perceiver needs to lack all interest in the object, e.g. the desire to possess it, for a pure aesthetic judgment of the object to be possible. Kant 1872, p50. Sosak Jederman, Hunger ist der Bestkoch, UND Ludenbong gesundem Appetit schmecktals, was nur es ist, Mithin du ein solches Wohlgefallen kein Wohl nach Geschmack. Nur wenn das Bier nicht befriedet ist, kann man unterscheiden, wer unterweilen Geschmack habe oder nicht. Geschmack ist das Bier des Vermogenseins Gegenstands oder einer Vorstellungsart durch ein Wohlgefallen oder Missfallen ohne als INTERS. Der Gegenstand ein solchen Wohlgefallens heißt schon. Our translation. People say that hunger is the best cook, and people with a healthy appetite enjoy everything that is edible. Such pleasure does not evidence a choice based on taste. Only when the needs are satisfied can one discern who amongst the many is taste or not. Taste is the ability to judge an object or a performance with pleasure or displeasure without any interest. The object of such a pleasure is called beautiful. Kant's view takes a highly restrictive position on aesthetic judgment, differentiating between pure, what we today might call objective, and impure judgments, effectively excluding most perceivers. It is also elitist. If such a pure and disinterested judgment is only available to the few people on this planet whose needs are met entirely, then aesthetic judgment is not available to the majority of humans. For an empirical approach to aesthetics, 388 Jesche Westphal Fitch and W. Tecumseh Fitch seeking broad commonalities between humans, Kant's view implies an overly restricted working model, and Baumgarten's previous, more inclusive approach is preferable. The later movement, influenced by the reports of explorers and adventurers describing the art practices of other cultures from around the world, explicitly argued that the aesthetic capacity is fully shared by all humans, as stated by Franz Boas. In one way or another, aesthetic pleasure is felt by all members of mankind. No matter how diverse the ideals of beauty may be, the general character of the enjoyment of beauty is of the same order everywhere. The very existence of song, dance, painting, and sculpture among all the tribes known to us is proof of the craving to produce things that are felt as satisfying through their form, and of the capability of man to enjoy them. Boas 1955, p9. Indeed, the pervasiveness of ornamental objects and patterns and their similarities in symmetry, repetition, and structure gave rise to the notion that common, describable elements might underlie ornament and that ornament could usefully be described in grammars. C.E.G. Jones 1856. This approach has been greatly extended in more recent work by Washburn and Crow, 1988. 20.2.2 The multiple purposes of art. Louise Riefel, in his posthumously published Historische Grammatik der Bildenden Kunst, Historical Grammar of the Visual Arts, Riefel 1966, emphasized that humans naturally possess a Kunstschaffenstrieb, a drive to create art, Riefel 1966, p. 217. Riefel differentiates between three purposes, sweep, characterizing all human artifacts, 1. Schmuon decoration, 2. Gebrauchsweck, use, 3. Vorstellungsweck, imaginative purpose, Riefel 1966, p. 217. There may be mainly functional creations with little artistic content, e.g. an arrowhead, and almost purely artistic creations with no actual functional purpose other than decoration and / or representation. The intertwining of function and aesthetics in tools is particularly interesting. Some quite early hominid tools, so-called bifaces or hand axes, first produced about 1.4 million years ago, within 1996, have a high degree of bilateral symmetry which would have required considerable planning and careful execution. The largest specimens weigh well over a kilogram and are 30 centimeters long, Van Bainsmith 2004, and it is not clear that they could have functioned usefully as tools. Both the size and symmetry of the Acheulean hand axes have stimulated discussion about aesthetic or social functions. Cohn and Midden 1999, Midden 2003, Noel and Chom 2009, and the concomitant cognitive abilities required to create them, Midden 1996, early in human cultural development. 20.2.3 Fechner in non-representational art. Fechner, 1876, distinguished between direct and associative factors in aesthetics. Associative factors correspond roughly to Riefel's Vorstellungsweck, the ideas and associations that an object triggers in the perceiver's mind. Direct factors are more closely tied to properties inherent in the object, such as symmetry, color, and other formal or material properties. Associative factors can potentially intensify or counteract the effect of the towards a comparative approach to empirical aesthetics. 389 direct factors. Therefore, Fechner suggested that in order to identify aesthetic principles, non-representational ornament may be more useful than representational art, because the associative factors in the objects portrayed in representational art can include or override the more subtle organizing principles. This is not the case in ornament, where formal organizing principles take center stage. The associations that a portrayed object triggers are very specific to a certain place and time, and thus hinder a comprehensive historical and cross-cultural study of aesthetics. Furthermore, direct factors are likely to be the only ones that can be meaningfully studied across species. Concerning data collection, Fechner proposed 3 different methods for empirical inquiry in aesthetics: wall, choice, Herstellium, reduction, and Verwindung, usage in the real world. The underlying assumption is again that aesthetic proclivities can be active in multiple modalities, and thus can potentially be broken down into component parts, some of which are shared across all cultures and potentially across species, although to our knowledge, Fechner does not discuss the latter possibility. Fechner's three-way approach takes into account that aesthetics is not a simple stimulus/response activity captured by a sender/receiver model. Inevitably, the producer, S, of an artwork/aesthetic object also engage their perceptual proclivities during production. Very often, the finished product differs from what was originally envisioned, presumably due to the effects of feedback from perception influencing production, leading to unexpected results and happy accidents. Biological approaches to aesthetics have only recently been proposed, and empirical data from animals is rarely included. Igor Bestfeld, 1988, writing about the biological underpinnings of aesthetics, distinguishes between 3 layers of perceptual biases that we might find: those that are shared with other species, specifically other vertebrates, level 1; those that are unique to the human species but shared across humankind, level 2; and those that are unique to a specific human culture, level 3. These are important distinctions worth keeping in mind when developing a comparative approach in aesthetics and can, in our opinion, be usefully extended to production biases as well. We hypothesize that Fechner's associative factors are located at level 3, while direct factors are situated at level 2. If true, this alignment again underscores the relevance of non-representational abstract art to cross-cultural and cross-species inquiry. The contents of level 1, aesthetic proclivities shared with other species, remain little studied and poorly understood. However, an increasing body of research on birds, insects, and primates, reviewed below, allows us to form tentative hypotheses about what may be shared among animals. 20.3 Some implications of non-representational human artifacts. Some of the oldest human aesthetic artifacts known are patterned markings on ochre dating back about 70,000 years, hence Hillwood et al. 2002, Kuhn and Steiner 2007. Contemporaneous perforated marine shells seem to have been collected and worn specifically for their visual appeal, hence Hillwood et al. 2004, Van Haren et al. 2006, Uzugger et al. 390, Jesche Westphal Fitch and W. Tecumseh Fitch 2007. Both predate Paleolithic representations of humans or animals by roughly 30,000 years, Hodgson 2006, Verputten and Eliason 2010. This is surprising, because geometric patterns are far rarer than animate beings in the natural world, and animals and fellow humans would have had a high relevance for early human artists. The fact that abstract patterns and ornaments can be found across cultures, including those that have not developed representational art, further supports the idea that decorative abstraction is a basic and direct outlet for the human aesthetic drive, with no general need for representation. Ochre has been used by humans for at least 100,000 years. Quite sophisticated ochre processing tools from that time have been found at Blombos Cave, South Africa, including an abalone shell containing a well-fitting grindstone, hence Hillwood et al. 2011. This toolkit contained a residue of the mixture used, consisting of ochre, bone, and marrow, charcoal, and other minerals, indicating that these humans were experienced in producing pigments. Ochre can be used for body painting, and still is in many cultures, but also for tanning, hafting, and other things, so its presence alone does not demonstrate aesthetic activities. Gastropod shells were used very early on as body decorations. Some of the oldest examples known date back 70,000-82,000 years, hence Hillwood et al. 2004, Van Haren et al. 2006, Uzugger et al. 2007. Some of these oldest examples show evidence of having been covered with or come into contact with ochre, hence Hillwood et al. 2004, Uzugger et al. 2007. Where marks around perforations in the shell suggest that the shells were suspended from cords, like beads, Uzugger et al. 2007. Ornamental shells have been found in locations several kilometers from the nearest beach, and due to their small size they were unlikely to represent a food source. Unlike the shells of mollusks that were used for food, shells used as beads show abrasion marks suggesting that they were collected after they washed up on the beach, rather than caught fresh, Kuhn et al. 2001. Around 30,000-19,500 years ago, beads began to be fashioned from teeth, bone, stones, and other materials, with further embellishments and patterns engraved into the surface. Dubin 1997. Beads from 38,000-10,000 years ago have been found in Australia, Africa, Russia, India, China, and Europe. Even today, beads are popular as jewelry, continuing one of the oldest aesthetic traditions of humankind. Darwin, 1874, discussed body ornament as the most basic form of art in the descent of man, and interprets it mainly as a means to enhance physical features and to increase physical beauty. He, Darwin 1874, p. 577, noted the universality of ornament, suggesting that it is due to a shared cognitive architecture. Lastly, it is a remarkable fact that the same fashions now prevail, and have long prevailed, in the most distant quarters of the world. It is extremely improbable that these practices, followed by so many nations, should be due to tradition from any common source. They indicate the close similarity of the mind of man, to whatever race he may belong. Towards a comparative approach to empirical aesthetics, 391 ornaments are produced and appreciated by men and women alike. In contrast, most famous painters, sculptors, architects, musicians, and poets in Western culture were men, which has led some to hypothesize that art production is mainly a male trait, while in 2003. However, a male preponderance in the arts is most likely due to socio-historical factors specific to Western cultures, where the aesthetic objects produced by women occupied the less valued domestic and craft domains. Everyday objects that may be subject to aesthetic modification such as weaving, carving, or sewing are produced by both sexes. Shiner 2001, although the allocation to the sexes may vary from culture to culture. Decorating the body with beads, tattoos, scars, or paint is extremely common, growing 1997, Dubin 1997, and is found in men and women alike, as well as in children. Interestingly, symmetrical paintings on the face increase the perceived attractiveness of faces. Cardenas and Harris 2006. Swadlin Cuthill, 1995, have shown that artificial manipulations of photographs of individual faces to make them symmetrical actually decreases their attractiveness. However, symmetry is preferred in images of faces created from many averaged faces. Herbert et al. 1999. It may be the case that symmetrical face markings are a means to make a perceiver focus on a general global symmetry, akin to averaging facial properties as in Herbert et al. 1999, while drawing attention away from characteristics that define an individual face, and individual facial asymmetries. Cardenas and Harris, 2007, found that women do not rate symmetry of the face or face decorations more highly during the fertile phase of their cycle, suggesting that at least symmetrical ornamentation of the face does not act as a straightforward cue allowing females to assess mate quality or good genes. In addition to looking attractive, body decoration probably always has been a social activity. It is difficult to tattoo or scar oneself, particularly when symmetry and regularity is the goal. CEG figure 20.1, thus weakening the obvious parallel between body ornament and animal courtship displays. Ornaments may thus serve a group cohesion function, see figure 20.2, or as a means for rapid broadcast of diverse social information to a large number of people beyond immediate associates. Kuhn and Steiner 2007. Verputten and Eliason, 2010, have proposed sensory exploitation in combination with social learning as a mechanism by which representational art evolved in humans. Sensory exploitation is a mechanism on the part of the sender of a signal, manipulating the signal to heighten its salience to the receiver due to pre-existing perceptual biases. Ryan 1998. Verputten and Eliason argue that the early rise of non-representational art and geometric patterns can be explained by stimulation of lower, e.g. primary visual cortex, visual areas. It required social learning and rituals, in addition to an emerging mental bias for iconic images, e.g. readiness to detect faces or figures in inanimate matter, for iconic art to emerge in human society. They thus attempt to map the cultural evolution of artistic tradition onto neural processing in the visual system, with abstract patterns being both earlier in history and lower in the hierarchy. Although intriguing, we find this argument unconvincing. Not only has it been shown that symmetry perception does not primarily activate early visual cortex, Sasaki et al. 2005, but as already observed, abstract art is often a social art form. The postulated basic 392 Jesha Westphal Fitch and W. Tecumseh Fitch manifestations of aesthetic behaviors may be more sophisticated than previously thought, and already involve higher-level visual processing and social interactions. Research with animals, whose basic visual system closely resembles that of humans, provides one way to evaluate this hypothesis. In another attempt to understand the origins of art, entoptic phenomena have been proposed as the trigger for early non-representational art. Lewis Williams endows in figure 20.1 an example of the intricate and highly symmetrical facial tattoos typical of Maori tradition in New Zealand. Figure 20.2 body ornament is often by necessity applied in a social setting, for example between mothers and children, left, or same-sex dyads, suggesting that aesthetics has a strong social core. Towards a comparative approach to empirical aesthetics 393-1988, Dronfield 1996. These are visual phenomena that arise not from stimulation of the retina by light but from activity within the visual system itself, for example, the flashes and geometrical patterns perceived when pressure is applied to the eyeballs, during exposure to stroboscopic flicker, or the visual aura perceived by many migraine sufferers prior to an attack. Given the similarities in the visual systems across species, this would predict that entoptic phenomena are not unique to humans, although testing this prediction is non-trivial. Thus the question of why only humans have developed the urge to produce abstract geometrical patterns remains open. Taking a broader view on the motivation to produce aesthetic objects, Deacon, 2006, suggests that aesthetics may be part of a general novel cognitive style that evolved in humans, involving a modified motivational system. Such an internal reward system would make it inherently enjoyable to perceive and manipulate certain visual stimuli in a manner that may also apply to music and language. Additionally, Deacon, 2006, p30, posits that humans have a unique representational stance which biases perception towards detecting symbolic relation between an object and another referent, e.g. interpreting cloud shapes as objects. This would explain the origin of representational art. Certainly, aesthetic experiences are rewarding, and it seems likely that the brain's reward system has a reinforcing effect on the production and perception systems underlying aesthetics. However, we suspect that the representational stance did not play an important role initially, given that geometrical patterns seem to be the oldest art forms and lack any obvious iconic representational function, although symbolic reference may arise later, e.g. meander patterns representing Greek culture. While it may be impossible to reconstruct the pathways by which geometrical patterns arose, the fact that they are expressed so ubiquitously across virtually all cultures as well as in the oldest artifacts suggests that they are part of our core aesthetic sense, and thus make them a good departure point for considering research in other species. 20.4 Animal aesthetics. At least since the 1950s, claims have been made that chimpanzees and other primates produce artistic paintings when provided with paper, paint, and brushes. Other animals which have been claimed to have artistic abilities include elephants, horses, dolphins, and rhinoceros. We see these performances as having limited relevance. Animal paintings are only produced in a captive or domesticated setting, with human encouragement and provisioning of materials, suggesting that these paintings are more likely due to encouragement and rewards by humans than a natural artistic or aesthetic inclination of the animals. Unfortunately, little solid empirical work in the lab has been done specifically on the types of aesthetic perception that animals might have. However, using training and food rewards, Watanabe, Sakamoto, and Mukita, 1995, have shown that pigeons can discriminate between Monet and Picasso paintings and generalize the distinction to new paintings 394 Jesha Westphal Fitch and W. Tecumseh Fitch by other painters in a similar style. Pigeons can also be trained to distinguish between children's drawings that had been classified as good or bad by humans prior to the experiment, based on their own subjective judgment, and generalized to further, novel examples of these categories, Watanabe 2010. Even so, there is no indication that the birds are enjoying these experiences beyond the immediate food reward they receive for successful answers or that they prefer good over bad paintings. Indicators of enjoyment might be that the bird paused for a longer period of time near a given artwork without receiving a reward, viewed it for a longer time, or might be physiological measures such as lower cortisol levels or lower heart rates when exposed to art. Nonetheless, because pigeons have excellent vision, this research is valuable in showing that visual tasks relying on food rewards, measuring actual behavior and using artworks as stimuli can be successfully applied to animals without involving aesthetic appreciation as motivation, as would inevitably be the case with human participants. Perhaps more convincingly, Watanabe Nemoto, 1998, provided Chaviscaros, Pata or Izabra, a choice between perches which either elicited playbacks of Bach and Schoenberg or silence. 2 of the 4 birds spontaneously spent more time on the perch that triggered Bach's music. Accepting that this may reflect some preference on the bird's part, the question of what aspect of the stimulus is preferred, loudness, tempo, pitch, range, etc., remains open. Cf. Fitch 2006. Early evidence suggested that non-human primates prefer regular to irregular visual shapes. Wrench, 1957, studied visual preferences in a capuchin, C. bus apella, and a vervet monkey, Cercopithecus ethiops, now Chloro C. bus ethiops, with stimuli that either contain symmetry on one or two axes, regular, or were asymmetrical, irregular, and reported a bias in both species towards the symmetrical shape. Anderson, Kawahara, Kuroshima, Lady, and Fujita, 2005, later conducted a similar study with 4 capuchin and 4 squirrel monkeys, Samurai Sirius, with additional stimuli including A. Images of bilaterally symmetrical versus scrambled faces, and B. Geometrical shapes that were arranged regularly but not in a bilaterally symmetrical fashion versus scrambled shape arrangements. Regular or irregular images were pasted on cards and several of them presented simultaneously to the animal. The first card to be picked up was interpreted as the preferred image. The animals did not receive food rewards. There was a slight preference for regular over irregular patterns, but this was not consistent for all individuals of a species and not always statistically significant. However, even when not significant, the trend tended to be against irregular and for regular patterns. Again, it is not clear that the animals gained any aesthetic pleasure from this task, and there is no evidence that these species produce such regular patterns. Nonetheless, these results may indicate a subtle perceptual bias for regularity in other primates that might be utilized and reinforced in human aesthetic artifacts. Walker, 1970, exposed rats to backgrounds ranging from monochromatic gray to black and white geometric patterns of varying complexity and found a general tendency for the animals to move from less complex to more complex stimuli during the day. Walker, 1970, p. 643. As the order of the backgrounds was not counterbalanced, this effect may have merely been due to familiarity or novelty-seeking behavior in the animals. Towards a comparative approach to empirical aesthetics, 395 artificial body ornaments in the form of light bands change preferences for conspecifics in zebra finches, Tenayapi jugutata, and can have a positive effect on both males and females. Zebra finches have orange red beaks, and males additionally have orange red patches in the face. Females prefer males with red bands over unbanded individuals or those with blue and green bands, while males prefer females with black or pink bands. Early ETAL 1982. When males are kept in dyads, those equipped with red bands monopolized food sources and displaced individuals with green bands. Cahill ETAL 1997. Recently, Pariser, Marriott, and Griffith, 2010, reported that when wild-caught zebra finches were kept in male-only aviaries, those individuals with red bands gained more weight and sang more than those individuals with green or neutral bands. Seguin and Forsmeyer, 2012, however, failed to replicate this effect with zebra finches bred in captivity. We note that ultraviolet light seems to play a crucial role in the preference for red, and that artificial lighting may distort the UV information available to the birds. Hunt ETAL 1997. This may explain the difference in these two studies. Studying the aesthetic experience as a monolithic whole in animals and comparing it to that of humans can only provide the coarsest insights into the biology and evolution of the aesthetic sense. Particular species may have similar abilities and proclivities in some parts of the aesthetic process, but not others. We suggest a modular approach. In the visual domain, perception can be broken down into perception of color, symmetry, reflectional, rotational, translational, repetition, Gestalt principles, for an early study see Hertz 1928, and so on. Production could be broken down into production contexts, production self-reward systems, i.e. the effect that producing something has on the producer itself, demonstrating the ability to manipulate objects and use tools, self-adornment versus object adornment, etc. We now explore some commonalities and differences between bees, birds, and primates concerning production, nest building, and symmetry perception. 20.4.1 Nest building. Nest building is an intriguing behavior to examine in the context of aesthetics because it characterizes all great apes, most birds, and many bees and wasps. Not only does nest construction entail a sophisticated use of external material, but in many species cooperation and quality assessment by perceivers play a role as well. Bees produce a wide range of nests, using sand, leaves, clay, feathers, or wax. Von Frisch 1974. The honeycomb produced by honeybees, Apis mellifera, is particularly pleasing to our eye because of its astonishingly regular hexagonal pattern. Many bees work together to produce the comb. A single cell may be constructed by multiple bees by placing wax chips at 120 degrees to each other to form the walls of the cell. Von Frisch 1974. The entire comb structure is independently aligned by many bees along a line determined by the Earth's magnetic field. The production of the comb cells is dependent on motor sensory feedback from bristles on the side of the bee's neck, and ceases when these are immobilized. Von Frisch 1974. The hexagonal shape of the cells can also be found in other species of bees and wasps, which use non-wax building materials, so that the hexagons are unlikely to be 396 Jesha Westphal Fitch and W Tecumseh Fitch due to properties of the wax. Contra per ETL. 2004. This fact taken together with the experimental results reported by Von Frisch refute the oft-repeated myth, originating with Darcy Thompson, 1948, that regular hexagonal cells emerge automatically due to physical principles. Instead, these structures seem to require active, precise control of the insect builders themselves. The majority of bird species build nests and use them for parental care, although the complexity and materials of the structure as well as the social dynamics involved in nest building and courtship vary considerably. Hansel 2000. While females are typically involved in nest building, either alone or together with the male, there are some cases where females assess and choose between nests built by males. For example, weaver birds, Placidae. Male village weaver birds, Placers cuculatus, native to Africa, construct nests later inspected by females. See figure 20.3. The nests are attached to branches and consist of interwoven blades of grass. If a female proves, she will line it with grass and mate with the male. Hansel 2000. Thus, the female chooses her mate partially on the basis of the quality of the nest he can construct. Walsh, Hansel, Borello, and Healy, 2011, have shown that male southern masked weaver birds, Placers violatus, become more efficient builders over time. Nests of both species built late in the season are shorter and lighter than early ones. Walsh et al. 2010. This suggests that experience interacts with the bird's inherent drive to build nests, demonstrating that males are not merely performing an invariant fixed action pattern. Nest quality may thus reflect not only dexterity and physical prowess, but also the learning ability of the builder. While nest structures are typically used to incubate eggs, in some cases, the male construction is not related at all to incubation. Bowerbirds are a small family of birds, Telonringidae, native to New Guinea and Australia, Forjon 1986, Diamond 1982, consisting of roughly 20 species. In 15 of these species, Hansel 2000, males construct bowers in specially cleared courts in the forest. See figure 20.3. The bower, together with physical displays of the males, serves to attract females. Their use for the grousewap, in Rebel's terms. A bower is a large structure made from grass and twigs, somewhat reminiscent of a nest, that is built on the forest floor and decorated with various, typically brightly colored, objects. The preferred colors of the objects and construction style of the bower varies widely between species. The bowers are not used as nests, these are built by the female after mating. Rather, bowers are a component of the courtship display, serving to entice and impress the female. Rebel Schmielangswet. There is also competition between males. Neighboring males often try to steal objects from rivals' bowers and slash or destroy the bower structure. The dimensions and construction principles of the bowers vary between species, as do the types and colors of the objects used to decorate the bowers. While bowerbirds are famous for a behavior that appears purely ornamental, it is not unique to them alone. Other bird species are known to clear courts for their displays, Hansel 2000, and some species such as the superb lyrebird, Menura novae hollandi, additionally modify the center of the clearing with a mounted bird, superb lyrebird, or grasstop, Jackson's widow bird, Euplektes jacksonii. In the bird of paradise species lost towards a comparative approach to empirical aesthetics 397 Parachia loisii, males place selected objects in the clearings, reminiscent of bowerbirds, with the difference that females subsequently remove the objects from the clearings, Pruitt-Jones and Pruitt-Jones 1988. All adult great apes, gorillas, chimpanzees, bonobos, and orangutans build nests every night and use them for sleeping and sometimes for social interactions such as grooming. Sabater Pi et al. 1997. The nests also offer protection against predation in wet ground. Individuals build nests that they rarely share with others, with the exception of mothers sharing nests with their infants. Nests are rarely reused and are built anew each evening. As these nests are mostly arboreal with the exception of gorillas who usually build terrestrial nests, Tudun et al. 1995, the nests need to be sturdily constructed. An analysis of orangutan nests showed that the structures are complex, with sturdy branches preferentially used for support, and thinner branches used for interweaving. Van Kasteren et al. 2012. Nest construction in chimpanzees and bonobos is rapid, taking about a minute for day nests, used during midday rest, and no more than 5 minutes for night nests. Juveniles begin constructing nests in a playful manner, in preparation for their own solo nests that they must construct after weaning. Fruth and Holman 1996. To summarize, nest building is a behavior that in birds has the potential to be a crystallization point for the emergence of aesthetic production and perception due to its dual productive/perceptive nature, with competition in males driven by female perceptual judgment. In great apes, although nest building is a universal trait, there is little social pressure for this behavior to become more elaborate or fulfill a courtship function because each individual builds their own nest. In bees, we see that the collaborative construction figure 20.3 male weaver birds, left, construct elaborate nests that are inspected by the female prior to mating. Male bowerbirds, right, build bowers that do not function as nests, but serve to attract females. The construction is enhanced with attractive, colorful objects, and the male performs a display for the female, holding objects in his beak. 398 Jesha Westphal Fitch and W. Tecumseh Fitch by many individuals biases the group towards a unified production process, leaving no room for individual variation or innovation if the combined effort is to converge on a well-formed structure. Each of these examples shows certain points of contact with human artistic practices, but none possesses all of the relevant features. 20.4.2 Symmetry Perception Symmetry in particular, reflectional symmetry is an important element in many visual designs and is a highly salient cue for humans. For an extensive review on human symmetry perception, see Schroeder 2010. It has been hypothesized, Lure 1992, Penton-Boak et al. 1999, that symmetrical features and markings can act as indicators of high genetic fitness in humans and other animals, usually in males, with few deviations from a symmetrical ideal, fluctuating asymmetry, being indicative of good genes, meaning a high ability to deal with developmental stress and hence most desirable to females. However, fluctuating asymmetry has been criticized, e.g. by Palmer and Strobeck 2003, since the measurement of symmetry may be very sensitive to small measurement errors, especially in small traits, and asymmetries may arise for reasons other than developmental anomalies. Furthermore, Johnstone, 1994, argues that a preference for symmetry in females can arise in the absence of a link between symmetry and males in genetic fitness. Neural networks have been implemented to test whether a visual signaling process might inherently be biased towards symmetrical signals, similar to the symmetrical markings often found in animals. Enquist and Iraq 1994, Enquist and Johnstone 1997. While bilateral reflectional symmetry does tend to emerge in these models with repeated iterations of initially random visual signals, critics have noted that this effect may be a byproduct of the simplified perceptual models implemented. Dawkins and Guilford 1995, Bullock and Cliff 1997, Kamel et al. 1998. Both biological approaches make interesting and valid points but fall short of capturing human symmetry processing in its full generality. In animals, symmetry preferences have been studied extensively in the context of mate choice and sexual selection. North and Thornhill 1998. Far fewer studies have been published that examine symmetry preferences outside of a mate selection context. Since symmetry preferences in humans can be found in many contexts and feature prominently in many, if not most, human artifacts, we review research on symmetry perception in animals beyond the context of mate selection to see whether clues can be found in other species concerning the socio-ecological pressures that might have led to such an expansion of symmetry use in humans. Honeybees can be trained to discriminate bilaterally symmetrical visual stimuli from asymmetrical stimuli and can generalize to new exemplars. Gierfa et al. 1996, Gierfa and Menzel 1997. Although there was no initial preference for symmetrical images, after exposure those trained to approach symmetrical stimuli performed consistently better and hovered longer and nearer to the stimuli than those trained to approach asymmetrical stimuli. Bees can also distinguish a vertical axis of symmetry from other orientations in bilateral symmetry. Forge 1996. Bumblebees raised with no exposure to flowers or towards a comparative approach to empirical aesthetics 399 other symmetrical visual stimuli nonetheless show a marked preference, measured by approaches and staying times on the stimulus, for bilaterally symmetrical over asymmetrical images. Rodriguez et al. 2004. Given that these species obtain food from flowers, which are typically highly symmetrical, with more symmetrical flowers containing more nectar than less symmetrical flowers, for 1995, it is not surprising that symmetry is a salient cue to these insect species in a foraging context. Turning to birds, extensive studies have been carried out on symmetry perception in both pigeons and starlings, with contradictory results. Pigeons can distinguish bilaterally symmetrical, with a vertical symmetry axis, from asymmetrical stimuli and generalized to new exemplars, Delius and Havers 1978, Delius and Nowak 1982. However, Huber and colleagues, 1999, call into question whether this discrimination was based on an abstract concept of symmetry. Using 3 types of stimuli classes, they show that pigeons can learn to discriminate between symmetrical and asymmetrical items in 2 out of 3 stimuli classes. However, in the successful cases, the birds do not seem to acquire a general concept of symmetry to differentiate the 2 types of images. Instead, the authors suggest that pigeons use alternative discrimination strategies, the main one being rote learning. Results indicate that pigeons store each training exemplar together with the reward contingency. When viewing novel stimuli, the birds seem to compare the stored exemplars with the novel ones and respond according to a threshold based on stimulus similarity. A mixed picture is also emerging for European starlings, Sturnus vulgaris. Starlings have a speckled breast, and the difference between the number of dots on each side averages about 9 per center. Swadlin Witter 1995. The birds can differentiate between artificial symmetrical and asymmetrical dot patterns where the asymmetry is achieved by moving the dots of one side of a bilaterally symmetrical pattern around randomly without removing them. That is, the number of spots on either side remains the same. Swadlin Pruitt-Jones 2001. However, if the number of dots is increased and the asymmetry is brought about by randomly removing dots from one side of the bilaterally symmetrical image and placing them randomly on the other side, the number of spots on either side differs. Birds fail to discriminate between symmetrical and asymmetrical. Swadlin Ruff 2004, corroborating the findings of Huber et al. 1999, with pigeons. Similarly, young chicks, Gallus gallus, can be trained to discriminate bilaterally symmetrical stimuli from asymmetrical stimuli, Mascalzoni et al. 2012, but they have a preference for asymmetrical stimuli right after hatching. Furthermore, they preferentially peck on irregular dot arrays deviating from a straight line rather than arrays that are spaced along a straight line, Elliott et al. 2012, suggesting that a capacity to perceive mirror symmetry is not necessarily an indicator of a general preference for regularity in order. Taken together, the studies for pigeons, starlings, and chickens tell a cautionary tale. Symmetry detection can be achieved with training and positive feedback under some circumstances, but it is not a robust capacity as it is in humans. The detection of symmetry, if present in a species, may be confined to narrowly delineated circumstances and stimuli types, e.g. mate choice or foraging, rather than indicating a generalized perceptual principle, as it seems to be in humans. 400 Jesche Westphal Fitch and W. Tecumseh Fitch. The literature on non-human primate symmetry perception is surprisingly sparse. A brain imaging study conducted by Sasaki and colleagues, 2005, while participants were viewing radially symmetrical and asymmetrical dot patterns showed that the same areas of extrastriate visual cortex are activated in both humans and macaques, regions V3A, V4D, but that the activation was stronger in humans. There was little to no symmetry-specific activation in primary visual cortex, V1 and V2. These findings suggest that the visual processing of symmetrical stimuli in humans uses similar visual pathways as in other primates. Wade and Little, 2006, showed macaque symmetrical and asymmetrical versions of conspecific faces, and the animals look longer at symmetrical faces. Longer viewing time, at least in humans, is usually interpreted as a sign of preference. Langlois et al. 1987, Quincy et al. 1996. In an eye tracking study, Kano and Tomonaga, 2009, showed chimpanzees and humans images of humans, chimpanzees, and other mammals. The basic skin patterns of images were very similar, focusing mainly on the head and face regions of the images and spending little time on the background. This again suggests that perceptual similarities exist between humans and other primates. To our knowledge, no face preference studies have yet been conducted in chimpanzees. However, there is evidence that chimpanzees have no preference for symmetrical versus asymmetrical images of perineal swellings in female conspecifics. Rowe et al. 2012. Based on the scant data available, one possibility is that the basic perceptual processes involved in symmetry perception may be quite similar in humans and other primates. So far, in all animal species studied, symmetry recognition is restricted to particular symmetry types, typically reflectional symmetry, and contexts, mate selection in birds or foraging in bees, which may reflect a shared canonical neural substrate, Cohen and Zaidi 2013, V2, that relies on relatively simple perceptual mechanisms, Osorio 1996, Cohen and Zaidi 2013, that possibly evolved due to the biological relevance of symmetrical input in certain circumstances. The very broad appreciation of multiple types of symmetry that humans show, particularly involving both the perception and production of geometrical patterns, is to our knowledge unparalleled in the animal kingdom. Despite the rarity of flexibly generated, creative geometrical patterns in the animal kingdom and their ubiquity in human society, surprisingly little empirical research has focused on human pattern production, although cf. Westphal Fitch et al. 2012, 2013, and we think that the ability and proclivity of ordinary humans to generate structured and attractive patterns should be an important focus of future work in empirical aesthetics. 20.5 Discussion over its long history. Aesthetics has grappled with the distinction between a natural aesthetic appreciation and further development, or refinement, of aesthetic sensitivities through cultural input. The aesthetic traditions of a culture may vary over historical time, but while fashions come and go, we suggest that there are some core fundamental biases and proclivities of natural aesthetics that drive humans to produce aesthetic objects and remain unchanged. Towards a comparative approach to empirical aesthetics, 401 in particular, a very general ability to both perceive and produce symmetrical stimuli appears to be a stable, and biologically unusual, feature of our species. Production of highly ordered but also extremely varied abstract geometrical patterns is, according to current knowledge, unique to our species, as is the production of representational art. Although there are phenomena reminiscent of aesthetic behavior, e.g. bower building, in the animal kingdom, these nonetheless differ in important ways from those of humans. Restriction to certain contexts, males only. The development of symmetrical signals in the animal kingdom is frequent but again typically restricted to specific contexts and forms. Little is known to what extent abstract patterns are perceived in animals, but it seems clear that patterns are not generated in a creative, flexible, and open-ended fashion in non-human species. 20.5.1 Music, language, and art is a cognitive triad. Art, music, and language are cultural phenomena that have a strong social component. Language facilitates communication between humans and is typically used in a social setting. There are exceptions such as babbling and self-directed speech. Music is often played or sung in a group, and an audience may be present. Art is less obviously social, although artifacts may be produced and perceived in a solitary setting. Often they are produced in a group, particularly in traditional societies. In particular, body art is highly social both in its production and in its later intended perception. Besides their social functions, we suggest that a further common feature at the heart of the music/language/art triad is the ability to apply generative rules iteratively during their production, i.e. a generative syntax. In the case of visual art, we refer here in particular to abstract geometric patterns. Syntactic rules that govern the combinatorics of words are studied extensively in language, and it is a promising research field in musicology. Temporally 2010. We argue that some sizable subset of aesthetic behaviors involving abstract patterns in the visual domain also involves repeated application of generative rules with parallels to musical and linguistic structure. For example, see figure 20.4. Art, music, and language are all produced over time and the generative rules are applied serially during production. The ordering in the visual domain is less strict than in the auditory domain. Production may be restricted to a serial one element at a time production style, for example during sewing or beating, when only one joining operation can be executed at a time, but the order in which elements are joined is typically flexible. A more striking difference between visual art on the one hand and music and language on the other becomes obvious during perception. While listening to speech or music, the stream must be parsed serially over time. Thus, the perceptual process must closely track the production process of the speaker or performer temporally. However, eye tracking studies show that this is clearly not the case in visual art. Perceivers can scan the two-dimensional array, or three dimensions in the case of sculptures, anyway and in any order they like, without temporal restrictions. Humans, disregarding certain clinical groups, have a strong tendency to take in the entire artwork or stimulus first, focusing on details. 402 Jesche Westphal Fitch and W. Tecumseh Fitch at a later stage. Also, the perceiver can return their attention to regions that have already been looked at as often as they like. This relatively unconstrained aspect of visual perception versus the temporally bound perception of music and language offers a noteworthy freedom to the perceiver. Of course, this applies to static artwork but not to film or dance, which share the temporal flow of music or speech. It may be that such oppositions between visual and auditory, or static, and temporally dynamic input have a profound effect on our aesthetic experience. However, it is also possible that all aesthetic experience shares certain common organizing principles, for example an aesthetic trajectory of recognition/surprise and resolution regardless of the medium or temporal dynamics. Fitch et al. 2009. Both possibilities provide issues for exploration in future empirical work. Language is limited in its generativity by pragmatics and semantics. While it is possible to utter sentences such as colorless green ideas sleep furiously, meaningless sentences are not conducive to successful communication, which is usually the goal of speaking. Music and abstract art are not similarly limited by semantics. Music is the most abstract case, and art can be representational, i.e. convey representational meanings, or abstract. Abstract patterns are particularly visually striking, have the longer developmental history, as we have argued above, and are much more widespread across cultures than representational art. Both music and visual art have an additional dimension of flexibility due to the freedom from semantic content, optional in the case of visual art, that language does not typically enjoy outside the narrow domains of linguistic examples or Dadaist poetry. A12345612345B figure 20.4 The production process underlying two visual patterns produced from basic shapes, squares, triangles, using a rule that only two edges may be joined at each step, as when sewing patchwork. The repeated application of the generative rule results in binary branching structures that show multiple levels of hierarchical embedding. A. The number of nodes is odd, leading to an asymmetrical binary tree, while the nodes in B are even, resulting in a symmetrical, recursive structure. The branching direction in A is arbitrary, but is kept consistent in the diagram for clarity. Towards a comparative approach to empirical aesthetics 403.20.5.2 outlook precisely because of the vast variance in the types of artwork that humans produce, empirical aesthetics needs to cast a wide net to achieve a comprehensive picture of the human aesthetic drive, and to discover features that all cultures have in common. Therefore, we maintain that in the future, empirical aesthetics should in principle incorporate the aesthetic judgments and activities of humans from a wide variety of cultures, and include manifestations of the aesthetic drive that can feasibly be studied in the lab. In particular, we strongly question the notion that it takes special knowledge or formal education to have a fully fledged aesthetic experience. Fitch and Westphal, Fitch 2013. In the same way that linguistics, and more recently, musicology have both rejected traditional prescriptive approaches to what is good or bad or right or wrong, empirical aesthetics needs to embrace a non-elitist, cross-cultural approach which recognizes and explores the aesthetic capacity of ordinary humans. A broad comparative approach to aesthetics both across different human cultures and cross-species comparisons will allow the field to benefit from methodologies and research questions of linguistics and musicology, which have already mostly transitioned from a prescriptive, i.e. normative, to a descriptive approach, e.g. Honing 2011. We suggest that a wholehearted embrace of such a broadly comparative perspective has rich insights to offer into aesthetics, and the intriguing hidden structural similarities of the human cognitive triad of music, language, and art. 21.3 Functional connectivity. Statistical studies on the synchrony of firing can identify the existence of a functional connectivity of brain areas. First in ETAL 1993, first in ETAL 1995, defined as the statistically temporal dependency of neural activation patterns of anatomically separated brain regions. Van den Heuvel and Hulshoff, Paul 2010. Using functional connectivity to posit the existence of neural networks is a common procedure. In order to obtain such connectivity, temporal series of activation/deactivation of presumably synchronized neurons must be compared. As is well known, such temporal series can be obtained by means of functional magnetic resonance imaging, fMRI. This technique detects changes in blood oxygen content in brain areas. What, following Ogawa and colleagues, 1990, is called blood oxygen level dependent, BOLD, signals due to activity along a determinate span of time. Combining temporal series of BOLD signals and advanced statistical means of analysis such as graph methods, brain architecture consisting of modules of neural functional connectivity can be determined. A review of the literature on the resting state functional architecture carried out by Liu, Smicer, and Shimony, 2012, reported the identification of 7 networks. Apart from the DMN, these networks correspond to different particular processes ranging from relatively simple perception to higher cognitive achievements. Figure 21.3 shows the correspondence between he and colleagues, 2009, modules and cognitive systems. If the cognitive process, whose neural correlate is sought, maintains its activity during a considerable length of time, then fMRI can be used as an accurate technique to obtain connectivity patterns. However, compared with the relatively stable condition of subject's brain activity during resting state, aesthetic perception refers to cognitive processes taking place over a much shorter period. Selakonda et al. 2004. Variations of BOLD signals along several seconds are not accurate enough to detect such changes, since networks might be modified in a relatively narrow time during aesthetic processing tasks. Some studies have focused on dynamic changes in brain networks using fMRI techniques, Bassett et al. 2011, but their time windows cover several minutes. Therefore, to reach brain activation related to the perception of beauty, it is mandatory to use high temporal resolution techniques, like electroencephalography, EEG, or magnetoencephalography, MEG. EEG and MEG have high temporal resolution but less spatial resolution. For fMRI the reverse is true. We are thus facing a methodological dilemma. Either 1. We use a high spatial resolution to determine the distribution of active modules in the brain, but only averaging 414 Camilo J. Selakonda and Francisco J. Ayala a large period of time. Or 2. We choose to detect dynamic changes across short time spans, but thus can only obtain the modular structure of the cortical surface. A study of the dynamics of brain networks in aesthetic appreciation carried out by means of MEG offers some clues for explaining the persistence of DMN in aesthetic tasks. Selakonda et al. 2013. The authors obtained temporal series of brain activity for 24 participants during resting state and judgment of beauty of 400 diverse visual stimuli. They then estimated the synchronization in the theta band of the temporal series by means of Pearson correlation coefficient and phase locking value, PLV, Mormon 2000, Garita et al. 2006. The MEG signals were split into 3 temporal windows. Figure 21.4, top TW0, 500 milliseconds, prior to stimuli projection TW1, 25750 ms after stimuli projection TW2, 1500 ms after stimuli projection. Interwindow comparisons evaluated the differences in connectivity between temporal windows along each condition. Intercondition comparisons evaluated differences in connectivity between beautiful and not beautiful stimuli in each temporal window. Figure 21.4, bottom. Selakonda and colleagues, 2013. Results show that the neural connectivity present in the resting state is curtailed in the first temporal window, TW1, figure 21.5, top, being lateral view, medial view, top view, module I, module 2, module 3, module 4, module B, figure 21.3, association between modules and cognitive systems. Reprinted from +1, 4, he, y, Wang, j, Wang, l, etal, e5226, doi, 10.1371/journal.com.0005226. User rights governed by an open access license. Module 1, somatosensory, motor, and auditory functions. Module 2, visual processing. Module 3, default network. Module 4, attention processing. Module 5, limbic/paralimbic and subcortical systems. Art and brain. CO evolution 415 replaced by what the authors call the initial aesthetic network. This network mainly connects occipital regions. Figure 21.5, middle. The initial aesthetic network is nearly the same while viewing beautiful and not beautiful stimuli. However, during the second temporal window, TW2, significant differences depending on the judgment of beauty appear. The delayed aesthetic network identified in Selakonda and colleagues, 2013. Experiment consists of synchronized activity mainly present along medial occipital, lateral posterior parietal, medial frontal, and dorsolateral prefrontal in the left hemisphere, as well as in the right lateral parietal. Figure 21.5, bottom. The dynamic scenario during aesthetic appreciation seems to be, thus, as follows. 1. A starting point of high synchronization during the resting state, TW0. 2. This connectivity is curtailed during the first temporal window, TW1, and is replaced by a different network. 3. Part of the resting state networks is later recovered during the second temporal window, TW2. Both beautiful and not beautiful conditions share, during the second temporal window, a bilateral higher synchronization along frontal, parietal, temporal, occipital, lateral regions. This pattern matches the similar bilateral synchronization during the resting state. Due to its lateral position, this connectivity would have little relationship with immediately placed DMN. Hypothetically speaking, it is sound to claim that attentional tasks, obviously engaged in the aesthetic appreciation, would be responsible for this network. Figure 21.4 temporal windows and conditions compared in the analysis of brain dynamics during aesthetic appreciation. Reproduced from Camilo J. Selakonda, Juan Garcia Prieto, Jose J. Ramusco, Claudio R. Morasso, Ricardo Bello, Enrique Munar, Albert Flexes, Francisco Del Pozo, and Fernando Maistu. Dynamics of brain networks in the aesthetic appreciation. Proceeding of the National Academy of Science of the USA, 110, Supplement 2, pages 1045461, Figure 21.1, doi. Copyright 2013, National Academy of Sciences. Resting state aesthetic appreciation TW0 interwindows analyses interconditions analyses and beautiful and not beautiful vs not beautiful TW0 vs TW1 TW0 vs TW2 and TW0 TW1 and TW2 TW1 vs TW2 500 ms 0 milliseconds 250 milliseconds 750 milliseconds 1000 milliseconds 1500 milliseconds TW1 TW2 416 Camilo J. Selcondet and Francisco J. Ayala in turn. Differences of synchronization in favor of beautiful stimuli mainly affect medial parts of the brain. These differences are better shown in the TW2 intercondition analysis, which manifests that a higher connectivity exists in favor of the beautiful stimuli. Table 21.3 and figure 21.6, left. Not beautiful stimuli do not show any higher synchronized link. Table 21.3 and figure 21.6, right. We are looking at the delayed aesthetic network and figure 21.7 shows it from different perspectives. Figure 21.5 differences in synchronization while viewing beautiful, left, and not beautiful, right, stimuli. Top, TW1 TW0. Bottom, TW2 TW1. Reproduced from Camilo J. Selcondet, Juan Garcia Prieto, Jose J. Ramisco, Claudio Armarazo, Ricardo Bejo, Enric Munar, Albert Flexus Francisco Del Pozo, and Fernando Maestro, Dynamics of Brain Networks in the Aesthetic Appreciation, Proceedings of the National Academy of Science of the USA, 110, Supplement 2, pages 1045461, figures 21.2 and 21.3, doi, copyright 2013, National Academy of Sciences. PTW1 BPTW1 and BPTW0 BPTW0 and BPTW1 BPTW1 and B Art and Brain CO Evolution 417 Table 21.3 Number of MEG sensors and links more synchronized in the intercondition comparisons at P0.050. Beautiful not beautiful not beautiful beautiful sensors links TW06300 TW12100 TW2191000 figure 21.6 intercondition comparison in the second temporal window. TW2. Left. Higher synchronization for beautiful stimuli. Right. Higher synchronization for not beautiful stimuli. PTW2 and BPTW2 be back front figure 21.7 the delayed aesthetic network from different perspectives. The delayed aesthetic network matches, in part at least, the default mode network of the resting state. As we will see, this coincidence may throw some light on the elusive question of the evolution of the human aesthetic capacity. 418 Camilo J. Selcondet and Francisco J. Ayala 21.4 Perceiving beauty as a human trait neuroaesthetics experiments have been normally carried out with very specific groups of subjects, college students from developed countries in most cases. However, aesthetics, i.e. artworks, are found everywhere, impinging on people the ability to recognize products of other cultures as artworks. This universality is, in the opinion of Carroll, 2004, an argument in favor of considering the proposition that art may serve universal adaptive purposes. Theoretically speaking, a trait can be universal because it has been inherited from an ancestor who fixed it plesiomorphy thus being shared with other species belonging to our human lineage. Alternatively, we may consider that the trait was developed as a new feature apomorphy quite early in our species. In this second case, all modern humans would have the capacity for appreciating beauty, but no other species would share this trait. However, this universality poses a problem. As it is well known, brain tissues are metabolically expensive. Resting state activity most likely accounts for the major cost, in terms of energy, of running the brain. Rachel 2011. In the awake resting state, the brain accounts for 20% of the total oxygen consumption of the body, despite the fact that it represents only 2% of body weight. Gusnard and Rachel 2001. It is difficult to justify how any brain-related capacity would have become fixed during human evolution without explaining its benefits. Aiello and Mueller 1995. The adaptive advantages of aesthetic appreciation remain to be accounted for although a different possibility, considering it as an exaptation, exists. We will examine it later. The power of artworks to build communities of sentiments, promoting the cohesion of groups, seems to offer a conspicuous advantage. DeSandiaki 1992, 2007. Aesthetics would be a cohesive factor, thus adaptively convenient. Also, the emotional, i.e. hedonic, reward of art offers an explanation for the eventual selection of the capacity for appreciating beauty. See, for instance, Dutton 2003. Both reward and cohesion factors are good hypotheses to account for the current relationships existing between beauty and art. DeSandiaki 2009. But what can we say about their evolutionary journey? Although the phylogenetic appearance of the brain correlates for appreciating beauty cannot be ascertained, producing beauty seems less elusive. Works of art and decorative objects persist after the disappearance of their creators. Since painters or sculptors' works are durable, but dancing movements and music sounds are not, we will henceforth refer only to objects as artworks when speaking of the evolution of the human aesthetic capacity. When did this capacity appear? Although beauty, art, and aesthetics are different concepts that might be even in opposition, consider, for example, the movement known as ugly art. We will take these three concepts as being equivalent. A cautionary note must be stated. Since natural objects can be considered as beautiful by spectators too, the capacity for appreciating beauty might have evolved earlier and across more locations than did the production of actual artistic objects, created with the purpose of being aesthetically moving. In a similar manner, some spectators could consider as beautiful an object a lithic tool, for instance manufactured for practical purposes. Art and Brain CO Evolution 419. The lack of correspondence between artists' intentions and spectators' responses is well known, with many examples present in the recent history of art. Some examples include the popular reaction to the first Impressionists' exhibitions, or the initial reception of the Eiffel Tower. Therefore, the current consideration of lithic tools, or of any other object, as beautiful is not proof of either the intention of the artisans that produced them, or the eventual aesthetic appreciation of them by spectators at that time. Bearing this caution in mind, authors dealing with the phylogeny of aesthetics distinguish between objects that can be used as tools, like hand axes, and objects that do not have any practical benefit thus symbolic, such as decorative objects. In spite of the obvious utility of decorative pieces to express, for instance, social hierarchy, the symbolic criterion is useful. Non-practical objects belonging to the archaeological record are items of proof pointing to the appearance of aesthetic appreciation. A long-lived controversy between archaeologists, paleontologists, and anthropologists refers to the question of whether Neanderthals had the capacity to manufacture artworks. Some Neanderthal sites contain decorative objects. For instance, the Grotte du Rhin, Arcy-sur-Cure, France, has yielded a series of up to 36 objects, such as carved ivory pieces and perforated bones, the sole purpose of which must have been decorative. Hublin et al. 1996. Hublin and colleagues, 1996, interpreted the Arcy-sur-Cure artifacts as the result of cultural exchange. Dierco and colleagues, 1998, arrived at a different conclusion. Those objects were the result of an independent and characteristically Neanderthal cultural development, which had managed to cross the threshold of the symbolism inherent in decorative objects. White, 2001, has offered an alternative interpretation. It seems implausible that Neanderthals and Cro-Magnons independently and simultaneously invented personal ornaments manufactured from the same raw materials and using precisely the same techniques. Consequently, White defended the proposition that the Château-Brongnian ornaments from the Grotte du Rhin are ordination and were produced by modern humans. In addition to Arcy-sur-Cure, two other Neanderthal sites have provided perforated shells, Cueva de los Avions, genus Acanthocardia, Lysomeres, and Spondylus, with traces of colored pigment into the shell in Spondylus, and Cueva Anton, genus Pecten, both in Murcia and Spain, Silhau et al. 2010. Had Neanderthals reached this cognitive level? Dating of paintings found in Altamira, El Castillo, and Tigo Bustillo caves in Spain suggested provenances for some symbols and marks found of between 35,600 and 4,800 years, Pike et al. 2012, and some suggest they may be even older, Appenzeller 2013. If this is the case, arguments that suggest that the Neanderthals' decorative items are mere copies of similar objects manufactured by modern humans cannot be true. Our species would not have reached southern Europe by that time. Whether Neanderthals discovered decorative objects by themselves, or they imitated the manufacture and use from modern humans is not something that is easy to determine. Some proof of cultural sharing during the early Upper Paleolithic do, however, exist. Karavanek and Smith, 1998, documented the presence of two contemporary sites at Hrvatsko 420 Camilo J. Selcondet and Francisco J. Ayala Zaterki in Croatia which are close to each other. The Vindice cave has yielded Neanderthal remains, while Velika Pečina has only produced remains of anatomically modern humans. The authors believe that the similarities exhibited by the tools from both sites are due to imitation or even commercial exchange. These Croatian sites do not include ornaments, but they provide remarkable indications of cultural exchange. Nevertheless, the cognitive capacity linked to perception of beauty does not depend on skills for manufacturing decorative objects. If Neanderthals appreciated pendants enough to imitate, steal, or exchange them, it would be beyond doubt that they considered perforated shells and bones to be beautiful objects. 21.5 Patterns of the evolution of the brain. If Neanderthals and modern humans shared a similar capacity for appreciating aesthetic objects, the question would be whether we can link this capacity to Neanderthal brain characteristics. Emiliano Brunner, Giorgio Manzi, and Juan Luis Arzuaga, 2003, analyzed the transition from a generalized archaic pattern of the brain within the genus Homo to the modern and Neanderthal morphologies. Comparing metric variables and landmark data on physical endocasts and from virtual reconstructions based on computed tomography and three-dimensional image analysis, Brunner, Manzi, and Arzuaga, 2003, p. 15338, concluded that archaic and Neanderthal specimens share a common endocranial model, in which a large amount of variation is based on a single allometric trend. In this case, encephalization, viewed as cerebral volumetric expansion, structurally influences the variation in endocranial shape. This trajectory represents therefore continuous gradation, ranging from archaic small specimens to archaic larger ones, up to the extremely encephalized wormy Neanderthals. The archaic brain pattern shared by Neanderthals involves a relative reduction of the length and width of the occipital lobes, a vertical development, an enlargement of the frontal breadth, and the shortening of the parietal cord. The main difference with the modern human pattern of the brain refers to the parietal development of the modern morphotype, something that Brunner, Manzi, and Arzuaga, 2003, consider may have represented a key to surpass the encephalization constraints imposed by the archaic structural model. Expansion of the frontal lobes is an evolutionary trait shared by Neanderthals and modern humans, Brunner and Holloway, 2010. On the other hand, modern humans developed a neomorphic hypertrophy of the parietal volumes, leading to a dorsal growth in ventral flexion, convolution, characteristic of the cranial globularity of our species, Brunner, 2004. Roseman, Weaver, and Stringer, 2011, analyzed cranial morphological integration covariance of traits in a sample of 2,524 modern humans and 20 Neanderthals and concluded that the overall patterns are significantly different between the species. Nevertheless, Neanderthals' morphology is consistent with the modern human pattern of integration for more than 3/4 of the traits. To what extent these similarities and differences can affect neurological configuration cannot be assessed yet. Art and Brain CO Evolution 421.21.6 Comparative Studies. Human-derived features may also be distinguished by means of comparative approaches with non-human primates. Rowling and collaborators, 2007, offered a comparison between the brain activation in humans and chimpanzees during the resting state. These authors analyzed, by means of positron emission tomography, PET, anesthetized chimpanzees that, during the awake resting state, would have completely fixed radioactive glucose in the brain. According to the results, both humans and chimpanzees seem to coincide in the activation of medial and dorsolateral OFC, as well as medial parietal cortex, with the highest level of activity placed more dorsally in humans, BA9, BA32, and more ventrally, BA10, in chimpanzees. As Rowling and colleagues, 2007, found, during the resting state the strongly left lateralized activity related to language and conceptual processing in humans was absent in chimpanzees. Watanabe, 2011, obtained, also by means of PET, the default network curtailed in awake rhesus monkeys when attention-demanding cognitive tasks were performed. Watanabe, 2011, shows that as similar to the human default system, all monkeys showed higher rest-related activity in the medial prefrontal and medial parietal areas. Moreover, considering that the human default mode network is related to internal thought processes, Watanabe stated that default activity in the medial brain areas suggests that there might be internal thought processes in the monkey. Mentioning the chimpanzees case, Nordhoff and Panksepp, 2008, assumed that high degrees of self-relatedness correspond to high resting state neuronal activity. If Watanabe and Nordhoff and Panksepp are right, the similarities between monkeys, apes, and humans might indicate a self-relatedness capacity, shared to some degree. However, aesthetic capacity does not equal self-relatedness. The more interesting aspect of the comparative approaches is probably the strong left laterality identified by Rowling and colleagues, 2007, as a human trait not present in apes during the resting state. Let us return to the identification between the DMN and the aesthetic networks. 21.7 Aesthetic appreciation is an exaptation. It has been posited that aesthetic perception does not need to imply any adaptive advantage, since it could profit from other previously evolved cognitive characteristics with their own adaptive benefits. In other words, aesthetics might be just an exaptation. For instance, Kaplan, 1987, states that IT would be adaptive for animals to like the sort of settings in which they thrive. Thus, preference for landscapes would have led to preference for ornaments like gardens. Focusing on positive valence aesthetic appraisal, Brown and collaborators, 2011, hold that such a system evolved first for the appraisal of objects of survival advantage, such as food sources, and was later co-opted in humans for the experience of artworks for the satisfaction of social needs. Obviously, any hypothesis about this subject would be difficult to test. However, a complementary justification for the evolution of capacities for appreciating beauty may be 422 Camillo J. Selconda and Francisco J. Ayala given by pointing out the coincidence between the delayed aesthetic network and the default mode network. A fundamental function of the DMN is facilitating responses to stimuli. As Rachel and Snyder, 2007, held, intrinsic activity instantiates the maintenance of information for interpreting, responding to, and even predicting environmental demands. This functional capacity seems adaptive enough to justify by itself its metabolic costs, and it is performed by means of mind-wandering processes, in which DMN seems to play a fundamental role. A DMN phylogenetically fixed and linked to aesthetic perception is sufficient to justify such human capacity for appreciating beauty in objects. A different question is that of explaining how this link between DMN and aesthetic perception appeared, or, in other words, what characteristic of the default mode network might lead to the sudden experiences of the beauty of a picture or landscape. An added function of the DMN relates to mind-wandering processes. Mind-wandering refers to images, thoughts, voices, and feelings that the brain spontaneously produces in the absence of external stimuli. Stimulus-independent thoughts, SIT, Mason et al. 2007. The SIT are what we might call the mind talking to itself. Three possible explanations of the functional significance of mind-wandering were offered by Mason and colleagues, 2007. SIT enables subjects to maintain an optimal level of arousal. Alternatively, SIT adds coherence to one's experience past and present. A non-adaptive meaning was also posited. SIT could be a byproduct of a general ability to manage concurrent mental tasks obtained during human evolution. Although mind-wandering can be useful, the mind may wander simply because it can. Mason et al. 2007. Aesthetic perception is not stimulus-independent. Except in the case of recalling past experiences, detecting beauty depends on external stimuli. However, the aesthetic perception might be a byproduct of that general capacity for mind-wandering. Mind-wandering is a general process of perception neither guided by any goal, nor directed to any particular aspect. It obviously applies to the aesthetic appreciation of the environment. According to Kaplan, 1987, the move from appreciating landscapes to recreating them as artworks is supported by the coincidence between DMN and the aesthetic delayed network. Close to mind-wandering capacity for assigning beauty or ugliness to visual stimuli, from landscapes to artworks, could thus lead to continuous and very quick processes of aesthetic perception. Sudden comprehension that solves a problem or perceptual ambiguity has been detected, combining EEG and fMRI, Townios and Beeman 2009, Townios et al. 2008, as the culmination of a series of neural processes at different timescales leading to aha moments. Regarding aesthetic perception, our current study suggests that the appreciation of beauty might be an aha moment too, which appears at early temporal stages of the perceptive process, and is not guided by goal-directed tasks but works instead in an almost holistic way. In turn, the obvious advantages of the capacity for the appreciation of beauty, moving from the inner hedonic complacence to the satisfaction of social needs, Brown et al. 2011, would add adaptive advantages to further uses of such a trait. Not to surprisingly, aesthetic perception also activates regions, like the dorsolateral prefrontal cortex, DLPFC, linked to executive functions, Jacobson 2006, Vessel ETAL 2012. Heart and Brain CO Evolution 423.21.8 The question of qualia the internal, but stimulus-dependent visual appreciation of beauty is an individual instance of subjective and conscious experience what philosophers call qualia, Lewis 1929. The intriguing problem of qualia, i.e. the mind-brain relationship, can be stated as follows. How does the brain produce qualitative subjectivity? Searle 2011. In their study of consciousness, Crick and Cook put aside the hard problem of qualia, the subjective content of the mental states. No one has produced any plausible explanation on how the experience of redness or red could arise from the actions of the brain. Crick and Cook 2003. Instead, they focused on the soft problem, the neural correlates of consciousness. Regarding aesthetic appreciation, this soft problem, consisting of the localization of brain areas active when subjects gauge the beauty of a visual object, has been already solved, in part at least, by means of neuroaesthetics. Moreover, some aspects of the dynamics of aesthetic appreciation could help scratch the surface of the hard problem too. By means of a combination of fMRI, MEG, and behavioral studies of impaired subjects, it seems that the way in which the experience of beauty could stem from the actions of the brain may begin to move within our reach. However, current approaches to the hard problem yield only partial solutions. On the one hand, it seems that the structure of the qualia, consisting of a description of mental processes leading to the appreciation of the beauty of an object, can be accessed by means of scientific procedures. On the other hand, many personal circumstances, from previous experiences to character traits, health, age, perhaps gender, as well as the cultural and historical particularities of each subject and epoch, surely contribute to the experience of appreciating beauty. These aspects would modify, in a still not detailed fashion, subjective feelings. For the time being, the content of the qualia the eventual result of beauty, or its absence, as an inner sensation exceeds our grasp. Chapter 22 Art is a human instinct-led behavior emerging from the exaptation of the communication processes Luigi F. Agnati, Diego G. U. Dillon, and Kjell Fuchs 22.1 Introduction One extraordinary capability of the human brain is the production and appreciation of artworks, Young 1974. This capacity has usually been associated with the concept of beauty, a term notoriously difficult to define one and possibly related, in a broad sense, with the selection of palatable food and attractive mates that is also present in animals. This may be one of the reasons why appreciation of artworks and beauty itself are not coincident, why neuroaesthetics is not yet a well-understood field, and why important contributions from artists themselves are of a fundamental importance. Thus, we agree with Seekey's 2009 suggestion that the artist is in a sense a neuroscientist, exploring the potentials and capacities of the brain but with different tools. How such creations can produce aesthetic experiences can only be fully understood in neural terms. Such an understanding is now well within our reach. See also Maffei and Fiorentini 2008. Painters, sculptors, architects, and also novelists may be regarded as a special type of neuroscientist. See also Agnati ETAL 2012A, Lehrer 2007. In this chapter, Fernando Pessoa's masterpiece, The Book of Disquiet, Libro de Desasosco por Bernardo Soares, will be cited as it gives an extraordinary insight into the thinking of one of the greatest poets of the past century. Consistent with Seekey's quotation, our chapter will analyze if there are specific brain areas that are used in art appreciation, as indicated by neuroimaging investigations. A well-known and specific type of neuron that lies in these areas offers a special contribution in this regard. In view of the fact that the human brain is the result of a long evolutionary process, some general principles deduced from evolutionary studies may shed some light on the peculiarity of the human brain, in spite of similarities with other mammalian brains, especially in the primate order of mammals. The two concepts of exaptation, Gould and Verba 1982, and of tinkering, Jacob 1970, will be introduced together with a brief discussion on theoretical models of brain organization as well as on intercellular communication in the brain, something our group proposed in the last few decades. Agnati and Fuchs 1984, Agnati ETAL 2005, 2012b. Art is a human instinct-like behavior 427. Against this background, we propose a new interpretation of the morphological and neurochemical investigations on the human brain areas that according to neuroimaging studies are involved in the appreciation of artworks. 22.2 General premise 22.2.12 Basic concepts deduced from studies on evolution. The exaptation concept and the Russian doll model of living beings organization have both been applied to the modeling of the central nervous system, CNS, and offer a heuristic hypothesis on human brain-specific capabilities such as self-awareness. Agnati ETAL 2012b. In this chapter these concepts will be used to offer insights into unique human products, mainly artworks. 22.2.1.1 Exaptation is subtle but important distinction should be made between adaptation and exaptation with regard to their evolutionary roles. While adaptation refers to a feature produced by natural selection for its current function, such as echolocation in bats, exaptation has been defined as a feature that performs a function that was not produced by natural selection for its current use, e.g. feathers that might have originally arisen in the context of selection for insulation and not for flying, CEG Su ETAL 2012. However, natural selection may subsequently operate on such a new function to improve its adaptation to possible new environmental demands. Related to this concept, and focused on brain function, is Anderson's 2007-2010 concept of redeployment, or reuse, of a neural structure for a new function. There are obvious evolutionary advantages to redeployment of brain areas, and Anderson analyses this phenomenon in relation to cognition. We propose that the concept of exaptation can be used to shed some light on the neuropsychological aspects of artwork production by human beings from the Paleolithic to the present day. In addition, the redeployment of some brain areas and special types of neurons, namely, von Economos neurons, VENS, may be exaptated to contribute to this peculiar human capability. 22.2.1.2 The Russian doll model of the CNS and the concept of functional module. The concept of the functional module, FM, to some extent derives from the proposal of the modular organization of the cortex cerebri proposed already in the pioneering work of Laurent Deneau, 1938, and Mount Castle ETAL 1957, who introduced the concept of the cortical column. The existence of cortical integrative structures is not completely proven, Jones 2000, Tanaka 2003, as anatomical columns are not solid structures and modular structures occur also in non-cortical structures like the striatum, Olson ETAL 1972, Rockland and Ichino 2004, Rockland 2010. The relevance of the concept of a modular organization of brain circuits can be deduced by the theoretical consideration that such an organization can perform basic operations providing both compartmentalization and redundancy, which reduces the interdependence 428 Luigi F. Agnati, Diego G. U. Dillon, and Kjell F. Fuchs of components, enhances robustness, and facilitates behavioral adaptation. Furthermore, a modular organization also confers evolvability to a system by reducing constraints on change. Our proposal has combined the modular concept with Jacob's proposal that from a structural standpoint the living organism is organized as a nest of Russian matryoshka dolls, Jacob 1970, implying that smaller structures are buried within larger ones. Thus, our group has proposed that FMS are processing units organized according to a nested hierarchic criterion from cellular down to molecular level, Agnati and Fuchs 1984, Agnati ETAL 2012b. It should be noted that the hierarchic organization as well as the elements at each level are dynamically arranged and interconnected in order to carry out a task, i.e. the building of the Russian doll, and thus change with the functional state. Hence FMS are structural and functionally plastic modules without well-delimited anatomical borders, as seems to be the case for the cortical columns. Each FM is formed mainly, but not solely, by neurons and astrocytes, and at each miniature level the involved elements, e.g. cells, dendritic spines, or proteins, form a mosaic. The term mosaic has been introduced in order to convey the concept of topology. This may have a potentially large impact on the integrated functions of the assembly since it highlights the possibility that with the same set of tesserae, i.e. elements, markedly different mosaics can be assembled at a given level of miniaturization, which then become capable of a different way of handling information. The elaboration of the information can occur simultaneously at different miniaturization levels, GUIDEAL and ETAL 2011, but also sometimes in different temporal domains. The highest level of a horizontal elaboration is formed by mosaics of FMS, while the lowest level occurs at the molecular level, e.g. within multimeric protein complexes. In line with Hebb's classical hypothesis about the possible existence of cell assemblies interconnected by reverberating circuits, Hebb 1949, Wang 2001, it has been suggested that different FMS can be transiently interconnected to form a higher order mosaic and, as indicated above, a three-dimensional elaboration of the information is continuously in operation in the CNS, at NATA ETAL 2012b. 22.2.2 Volume and wiring transmission. In 1986 we published our original proposal on the existence of two main modes of intercellular communication potentially connecting all types of cells in the CNS, the wiring transmission, WT, and the volume transmission, VT, at NATA ETAL 1986. Our proposal was influenced by important contributions on communication in the CNS, Golgi 1914, Beeman 1978, Nicholson 1979, Schmidt 1984, and based on a number of observations, especially on the central monoamine neurons. For review see Fuchs and Agnata 1991, Agnata and Fuchs 2000, Desperries ETAL 2008, Newman 2000, Bakwarita 2005, Agnata ETAL 2010. The concept of VT introduced the extracellular space and the ventricular system as important channels for chemical transmission in the CNS. Complementary to synaptic transmission in VT is basically due to diffusion and flow of transmitters, ions, and trophic factors in the extracellular fluid, ECF, and cerebrospinal fluid, CSF. The basic dichotomous classification of intercellular communication in the brain proposed more art as a human instinct-like behavior 429 than 2 decades ago is still valid. However, evidence of the existence of new specialized structures for intercellular communication, such as microvesicles, C. Kokuxai ETAL 2009, and tunneling nanotubes, Rustum ETAL 2004, Bulika ETAL 2006, Gonkarava and Tarakanov 2008, called for an updating of our original conceptual model, Agnata ETAL 2010. The criteria which can be applied to characterize WT and VT and their subclasses have been deduced not only from structural and neurochemical findings but also from concepts and from the lexicon offered by informatics, Hopcroft and Ullman 1979. The sole and main criterion which allows differentiating WT from VT is the characteristics of the communication channel and more precisely the physical boundaries of the channel, which are well delimited for WT but not for VT. The classification can be further detailed by taking into account the other signal features. Some of these can be summarized as follows. Signal privacy. A signal is characterized by high privacy, i.e. a reserved signal, if only cells endowed with a specific recognition/decoding apparatus, as, for instance, specific receptors, respond to the signal. On the contrary, we deal with a low privacy signal, i.e. an open signal, when any cell reached by the signal can have access to it, e.g. CO2, H+. Signal safety. As far as safety is concerned, we deal with a safe signal if it is not altered during its diffusion from the source to the target cell and with an unsafe signal if it can be altered during its pathway. This occurs, for instance, to some VT signals that can be broken down or modified, e.g. by enzymes, or trapped in a cul-de-sac in the ECS pathways, Nicholson 1979. Connectivity. If the connections between cells can be rapidly formed or removed, they provide a dynamic network. On the contrary, the structure of a communication network is static when the pattern of connections is almost stable in time. Thus, WT may be better suited for a phasic, promptly acting, safe signal transmission to few precisely spatially defined targets. VT may instead be better suited for a tonic, slow acting, potentially unsafe signal transmission to many spatially disseminated targets. Accordingly, the synaptic type of WT in particular may mainly be present in the sensory input and motor output pathways where prompt acquisition of environmental information and a prompt motor response is needed. On the contrary, VT is mainly active in the resetting of the mood tone and, in general, in delayed and long-lasting emotional responses. However, it is most likely that all integrative actions in the brain involve strict cooperation between the WT and VT modes for intercellular communication. 22.3 Why human beings are artwork makers? This is central to the current chapter and will be afforded attention on the basis of the conceptually far-reaching words of the great British biologist, J.Z. Young. In an extraordinary book, Young, 1974, pointed out the fundamental relevance for the human beings of communication and especially of communication by symbols. Whatever status we may decide to ascribe to the mind, there is no question that the individual human being with his capacity for collection, storage, and transmission of information is a unit of 430 Luigi F. Agnata, Diego G. Dylan, and Kiel F. Uxe exceptional biological importance. After all, it is by individuals that the decisions are made that regulate human life. It is true that each can, in practice, survive only as a member of a society, but this is the corollary of the fact that he lives by acquiring and transmitting information. Young 1974, p10. Furthermore, he points out the special relevance of human artworks, but man's particular geniuses for the transfer of information between individuals and many subtle features are involved in his homeostasis. Communication by symbols is improved by all the agencies that we include as art, literature, and aesthetics, and these, far from being impractical, are major contributors to human homeostasis. Young 1974, p12. It is clear that the creation of beautiful and symbolic objects is a characteristic feature of the human way of life. They are as necessary to us as food or sex. Young 1974, p360. These inspiring sentences may help in introducing the concepts of instinct-like behavior and of psychic homeostasis. 22.3.1 The special human instinct-like for interspecies communication by symbols. The essential drive for interspecies communication by symbols that are vehicles of information not immediately related to basic needs seems to be a unique feature of the human evolutionary line, stretching back to ancestors of Homo sapiens living 164,000 years ago in South Africa, Marine ETAL 2007, and forward until the present times. This can be thought of as an evolutionary adaptation of the communication processes that are also present in other species for more basic aims such as survival of the single living being and reproduction of that species. In general terms, instinct, or innate behavior is the inherent inclination of a living organism toward a particular behavior. The simplest example of an instinctive behavior is a fixed action pattern, in which a very short to medium-length sequence of actions, without variation, is carried out in response to clearly defined stimuli. It is proposed that the exaptation of the interspecies communication processes in humans has led to the emergence of all the agencies that we include as art, literature, and aesthetic, as necessary to us as food or sex. These agencies are an essential human drive that can be thought of, in a broad sense, as a new instinct. As a matter of fact, the role of instincts in determining the behavior of animals varies from species to species. It is true that the higher up the evolutionary ladder, the greater is the role of the cerebral cortex. Social learning and basic instincts play a lesser role, but the highly evolved human brain could also allow, according to our hypothesis, the emergence of new uniquely human instinct-like behaviors. The fact that humans are bipedal, have hands to make tools, and possess complex brains are all biological features that have favored the emergence of the new instinct-like behavior of communication by symbols. However, these are necessary but not sufficient conditions to completely account for this emergence. A more probable and important aspect to consider concerns the process used by the brain to acquire knowledge about the world. As pointed out by Ziggy, 2004, such a process is basically a diffuse process of abstraction in which each FM possesses an abstractive machinery which transforms an incoming fragment of art as a human instinct-like behavior 431 sensation into a particular fragment of perception, Agnata ETAL 2012b, that is, it extracts a specific attribute of a sensory modality. The primary visual cortex represents a well-studied example of this strategy, see Carrera Perkin and Goodhill 2002. Mechanisms of binding, see Agnata ETAL 2012b, then allow these different components to be gathered into one picture, generating general models of the external world, Blakemore 1976. This process of generalization is a very efficient way in which a finite mind grasps the infinity of particulars and also frees the brain from total dependence upon a memory system, Ziggy 2004. However, there is also a price to be paid for this, which most likely became significant when the complexity of the brain permitted the realization of sophisticated abstraction processes. In fact, abstraction leads to models, ideas, and concepts, but our experience remains in the particular which may not always satisfy the ideal model formed in and by our brain. One way to obtain that satisfaction is to download CT 2004, The Ideas Formed in the Brain into a Work of Art. Paul Klee, a great artist as well as a commentator on art, wrote that art does not reproduce the visible, rather, it makes the invisible visible. Klee 1920, see figure 22.1. The peculiar importance of this communication of the human internal theater can also be understood with reference to the concept of psychic homeostasis. As pointed out in previous papers, see below, and also at Neta ETAL 2011, 2012a, human special status is the result of a continuous interplay between two types of homeostasis, the somatic and the psychic, which are strictly interconnected. 2.3.2 Psychic homeostasis versus somatic homeostasis. The classical term homeostasis originates from Claude Bernard, 1813-1878, and Walter Cannon, 1871-1945. Both proposed that the functions of apparatuses of a multicellular organism have as their final goal the maintenance of the constancy of composition of the internal environment. This is mainly composed of the liquid which surrounds the cells of the organism and by means of which cells exchange solutes and metabolites. This condition of dynamic constancy is called homeostasis. The maintenance of homeostasis implies an energy cost. Thus, McEwen, 2003, Gansel ETAL 2010, in his consideration of homeostasis, introduced three important additional concepts: allostasis, the process by which the organism actively adjusts the activity of its apparatuses in order to maintain the stability of the internal environment, notwithstanding the challenges due to changes of the external environment; allostatic load, which represents the cumulative energy cost to the body for the allostatic process; allostatic overload, a state in which the compensatory actions of the organism are overwhelmed and as a consequence serious pathologies can develop. The anthropocentric belief in the uniqueness of the human being is philosophically stated by the contraposition between residential extensa and res cogitans, Descartes 1960, that has led to a distinction between two elements of the human holistic complexity, soma and psyche. Accordingly, it may be proposed that not only is there a somatic homeostasis, which Luigi F. A. Neta, D. Ego Guido Ellen, and D. Kiel FUXE 432 figure 22.1 schematic representation of the communication channels between artist, artwork, and observer. The two panels give the possible basic steps involved in the imagery style and in the sensitive style. See Herbert Kuhn and Jaff 1983. The former communicates the author's fantasy or her personal experience expressed according to modules not immediately derived from reality and sometimes derived from her ideal world or even from her dreams. The latter one usually is more an attempt to give an faithful interpretation of the nature. In other words, the left panel represents the possible basic steps involved in an aesthetical evaluation of naturalistic artworks, sensitive style. The right panel represents the possible basic steps in an aesthetical evaluation of non-naturalistic artworks, imagery style. Artist's brain, elaboration of the ideal object hyperuranium, object in the mind of the artist artwork, new object in the environment artwork, object in the environment observer's brain, elaboration of the artwork observer's brain, elaboration of the artwork communication processes between artist and observer naturalistic aesthetical evaluation, matching between the environmental object, or its symmetry in the mind of the observer, and the artwork non-naturalistic aesthetical evaluation. Matching between the hyperuranium object, idea of the object in the mind of the observer, and the artwork environmental object artist's brain. Elaboration of the visual input art is a human instinct-like behavior. 433 is directed towards optimal somatic function, but there is also a psychic homeostasis, directed towards an equilibrated mental function. Agneta ETAL 2011, 2012a. Point 2 thus. The human organism in toto has as its main goal not simply the homeostasis of the internal environment but also a psychic homeostasis which represents a state of emotional balance, eudaimonia, that can be markedly altered during psychic disturbances, such as depression, paranoia, and post-traumatic anxiety. Recently, the concept of psychic homeostasis has been used to explain the possible functional role of dreams. Agneta ETAL 2011. In their relationship with sleep and dreaming, the homeostatic components operate by adjustments, using multiple dynamic feedbacks, of the various neuroendocrine systems. Such a resetting of the control and effector neural, vegetative, and endocrine systems also prepares the subject for future challenges. Hiroski ETAL 2004. This aspect was expanded, Agneta ETAL 2011, with the concept of predictive psychic homeostasis whereby the various feedback mechanisms bring the subject to a state of preparedness and anticipation for potential threats that may precipitate an allostatic psychic overload. Predictive psychic homeostasis is based on communicative social contacts, and it plays a fundamental role not only in the regulation of the internal somatic and psychic milieu, but also in relation to behavioral adaptations in social interactions. Agneta ETAL 2011, Shulkin 2011. As a matter of fact, psychic homeostasis depends greatly on social contacts where communication processes by means of symbols play a fundamental role. In this context, the relevance of production and appreciation of artworks that are instrumental for harmonious social contacts, and hence for the psychic homeostasis of the individual, becomes immediately clear. 322.3.3 Brain-body holistic system. The special two-phase homeostasis of the individual that can be deduced from the previous discussion leads to the view of the human being as a unique body-brain holistic system which operates owing to a specialized interface based on basal, hypothalamus, BH, especially paraventricular, and supraoptic nucleus, PVN, sun, and solitary tract nucleus, STN. As a matter of fact, STN receives direct neural visceral afferences from most of the peripheral organs while many blood-borne signals reach BH directly and STN indirectly. Hence, these brain regions are continuously informed about the body state as far as chemical parameters, e.g. glycemia, osmolarity, pH, and hormones, e.g. glucagon, insulin, adiponectin, cholecystokinin, are concerned. Thus, by affecting these interface regions, peripheral signals, neural, chemical, and hormonal, can orchestrate inter alia the central monoamine neuron systems and the release of oxytocin and vasopressin from neuroendocrine neurons, with oxytocin and vasopressin acting both as neurotransmitters and endocrine signals. These are major connections between the CNS and the body through which many psychosomatic processes occur. The importance of bidirectional, afferent communication should be emphasized. Both directions are important. Thus, the hypothesis has been introduced of a fundamental role of BH and STN and their reciprocal interconnections to maintain homeostasis via their combined actions on limbic structures, e.g. amygdala, and cortical structures, e.g. prefrontal cortex. Agneta 2012c. 434 Luigi F. Agneta, Diego G. Dillon, and Kiel FUXE. These basic mechanisms involved in the somatic homeostasis in mammals have been exaptated in humans to play a role in maintaining not only somatic homeostasis but also psychic homeostasis. Recently, a very important aspect of this complex control system has been discovered by Insel and colleagues. See Insel 2010, demonstrating that vasopressin and oxytocin released from central vasopressin and oxytocin pathways. See Romero Fernandez ETAL 2012, play a major role in social interactions, especially pair bonding. It has also been demonstrated by the Insel group, Insel 2010, that pair bonding may be brought about by increases in vasopressin, male, and oxytocin, female, transmission. Fuchs and CO authors, Fuchs et al. 2012, have pointed out the role of vasopressin and oxytocin VT in critical limbic regions of the mammalian brain, ventral pallidum, arginine vasopressin receptor binding, male, and nucleus accumbens shell, oxytocin receptor binding, female. Species differences in oxytocin and vasopressin receptor binding densities have been described. Gimbel and Fahrenholtz 2001. These results are consistent with the hypothesis that changes in neuroendocrine systems may evolve by changes in receptor distribution rather than by restructuring the presynaptic pathway. Wang et al. 1996. Thus, the increase of oxytocin and vasopressin VT could be brought about by rise of oxytocin and vasopressin receptor densities without a change in the density of oxytocin and vasopressin terminal networks. Fuchs et al. 2012. This means that behavioral differences such as pair bonding found in different species of the same genus may be caused by increasing the extrasynaptic receptor densities in critical limbic circuits for the diffusing VT signals, in this case the diffusing oxytocin and vasopressin signals from their nerve terminals in these limbic networks. As pointed out earlier, by 1986 Agnati and Fuchs proposed that monoamine and peptides, such as oxytocin and vasopressin, can also use the CSF as a pervasive diffusion pathway to reach target areas. It can therefore be stated that the reciprocal interaction between body and brain, mind, is a key concept in the study of integrated mechanisms of the human CNS not only for social interactions but also for the capacity to communicate by symbols. Thus, it is suggested that the holistic brain-body system is likely involved in the production/appreciation of artworks. 22.4 Artwork production/appreciation, a hub role for insula and anterior cingulate cortex. Neurology investigations in art, i.e. experimental neuroaesthetics, have focused on artwork appreciation despite the fact that the field should investigate both production/appreciation. Neuroimagining techniques have provided important findings, Nadal et al. 2008. However, further investigations on the neurobiological substrate should be carried out to clarify the following aspects at the very least: brain areas activated or inhibited in the appreciation of artworks, extension and boundaries of these brain areas, sequence according to which the brain areas are involved, time course of the electrical phenomenon within each brain area involved. Art is a human instinct-like behavior 435 as pointed out by Selikonda and colleagues, 2011. Until now investigations have been focused only on some selected aspects of aesthetic appreciation and have analyzed only some of the main neuroimaging features of the brain areas involved. Thus, current findings cannot do justice to the evaluation of the whole panorama of what constitutes the appreciation of beauty by the mind/brain. A further problem to be considered concerns the modern art forms, such as conceptual art, barely 2005, where the prime role of beauty has diminished, and is often actively challenged, Selikonda et al. 2011. Thus, researchers interested in the biological underpinnings of aesthetic experiences are faced with the problem of dealing with the several integrated mechanisms that are likely to underlie aesthetic appreciation versus beauty appreciation, and the underlying processes of perception, memory, attention, decision-making, reward, and emotion involved. Chaturji 2004, Letter et al. 2004, Nadal and Pierce 2011. Methodological reasons can justify some contradictory results of the neuroimaging investigations. However, as Chaturji, 2011, has rightly pointed out, a further challenge common to all neuroimaging studies should be considered, namely the basic problem of the reverse inference. In other words, it is not clear if such techniques can adequately deal with the interplay of such very cognitive, affective, personal, social, and cultural factors, and whether or not it is sufficient to consider activity in specific brain regions as proof of their involvement in a given cognitive process, for it should also be considered that somewhat different neuroimaging findings could be the result of a partially different, temporal and spatial, assembly of mosaics of FMS in different subjects, since this plastic process can be affected by the memories, emotional conditions, and cognitive capabilities of each subject. However, a revision of the available data has been proposed suggesting that aesthetic appreciation of painting, music, and dance involves a common pattern of at least 3 different kinds of measurable brain activity. Nadal and Pierce 2011. 1. An enhancement of low-level cortical sensory processing. 2. High-level top-down processing and activation of cortical areas involved in evaluative judgment. 3. An engagement of the reward circuit, including cortical, anterior cingulate, orbitofrontal, and ventromedial prefrontal, and subcortical, ventral tegmental area and nucleus accumbens, regions, as well as some of the regulators of this circuit, amygdala, thalamus, hippocampus. Let us focus on the orbitofrontal cortex, OFC, anterior insula, frontal insula, phi, and anterior cingulate cortex, ACC, as these have been found by several researchers to be the most commonly involved brain areas in aesthetics appreciation. Brown et al. 2011. The OFC occupies the ventral surface of the frontal part of the brain, plays a prominent role in general sensory processing, being a secondary sensory cortex for both olfaction and taste. Kring-Delbach 2004, Rolls 2004. The orbitofrontal cortex projects to several brain areas such as cingulate cortex, Carmichael and Price 1996, the ventral striatum, Ferry et al. 2000, head of the caudate nucleus, Kemp and Powell 1970, Haber et al. 2006, ventral tegmental area, Johnson et al. 1968, and the entorhinal cortex, Barbas 2007, providing a route for reward information to reach the hippocampus, Rolls and Siang 2005, and preoptic region, Rolls et al. 1976. 436 Luigi F. Agnati, Diego G. Dillon, and Kiel F. USC. The insular cortex is a portion of the cerebral cortex folded deep within the lateral sulcus between the temporal lobe and the frontal lobe, and it is divided into 2 parts, the larger anterior insula and the smaller posterior insula. It is approximately 30% enlarged. Indiana, the human relative to the macaque monkey, Seminiferi and Damasio 2000. The most strongly activated region by artworks corresponds with the anterior insula proper, a region associated with self-awareness, cognitive functioning, and interpersonal experience. According to several studies, this brain area is deeply involved in interoceptive awareness/insight. Critchley et al. 2004, Critchley 2005, a sense of the feeling self, Craig 2009, core effect, Barrett et al. 2007, the subjective experience of emotions such as pain, sadness, anxiety, and disgust, Leotti et al. 2000, and the capacity to anticipate the impact of emotional events on the body's responses, Singer et al. 2009. In particular, Craig, 2005, argued that the right anterior insula is associated with sympathetic autonomic activity, whereas the left anterior insula is associated with parasympathetic activity. By this reasoning, aesthetic processing should most likely be associated with the right insula due to its arousing nature. The anterior cingulate cortex can be divided based on cognitive, dorsal, and emotional, ventral, components. The dorsal part of the ACC is connected with the prefrontal cortex and parietal cortex as well as the motor system and the frontal eye fields, making it a central station for processing top-down and bottom-up stimuli. By contrast, the ventral part of the ACC is connected with amygdala, nucleus accumbens, hypothalamus, and anterior insula, and is involved in assessing the salience of emotion and motivational information. DeVue and collaborators, DeVue et al. 2007, have found foci of activity in phi and ACC in subjects when viewing their own faces as compared with viewing familiar faces of colleagues, suggesting that these foci may be involved in discriminating self from other. It could also be proposed that these brain areas are involved in judging human figures in paintings, above all portraits, and perhaps particularly one's own portrait. The presence of phi and ACC activations in the analysis of artworks raises an important question. Are there special types of neurons and/or a possible special organization of FMS in the insula and ACC that can be hypothesized as playing a role in the production/appreciation of works of art? In fact, a special class of neurons, the so-called von Economos neurons, VENS, are interesting candidates for a special role in the functional organization of insula and ACC 22.4.1 on the functional role of the von Economos neurons, VENS, 22.4.1.1 architecture of VENS. The VENS are large, bipolar cells that can be found in the cerebral cortex of only a group of species, including Cetacea, Beauty et al. 2009, Elephantides, Hakim et al. 2009, Great apes, and humans, Nijinsky et al. 1999. Characterized by relatively large brains. This finding led to the suggestion that VENS are a possible obligatory neuronal adaptation in very large brains, permitting fast information processing and transfer along highly specific projections and that evolved in relation to emerging social behaviors, Beauty et al. 2009. In art is a human instinct-like behavior 437. The human brain, they are located in layer 5 of only 2 cortical regions, the ACC and phi cortex, Biardo et al. 2008. More interestingly for their possible functional correlates are the observations on the qualitative and quantitative aspects of the vents, since they may possibly serve to identify differences between the human brain and the brain of other species. Allman et al. 2005, Premack 2007. The vents have a narrow dendritic arborization that spans the layers of the cortex and may be able to sample and rapidly relay the output from a columnar array of neurons. The apical and basal dendrites of the vents are remarkably symmetrical. This architecture suggests that the vents may be comparing inputs to these two symmetrical dendrites. The cell bodies of vents in ACC are, on average, 4.6 times larger than that of layer 5 pyramidal cells in this area. Nijinsky et al. 1999. The vent's large size suggests that they bear large, rapidly conducting axons, which is a characteristic feature of large neurons in layer 5 elsewhere in the cerebral cortex. Sherwood et al. 2003. Watson et al. 2006, has described in Miss Low-Stained vents the origin of the axon from the site of the soma. The dendritic architecture of neurons reflects the way in which they integrate information. Vetter et al. 2001. Both spines, Sabatini et al. 2001, and branches, Polsky et al. 2004, can operate as processing compartments and, compared with their layer 5 pyramidal counterparts, vents have fewer of both, which suggests that the von Economo cells receive, and therefore integrate, fewer inputs than pyramidal neurons. The radially polarized structure of the vents could be a specialization that facilitates the rapid radial signal transmission, providing an output response that reflects the integration of few, but likely, highly relevant inputs from the neurons of the neighboring FMS 2.4.1.2 localization and possible functions of vents as mentioned earlier. The phi is involved in self-awareness and decision-making under uncertain conditions, and it has been found to be consistently activated by peripheral autonomic changes. The activity of anterior insula also varied as a function of uncertainty during the anticipatory period in a gambling task. It has, therefore, been proposed that the vents and related circuitry are involved in rapid intuition which, like perceptual recognition, involves immediate effortless awareness rather than the engagement of deliberative processes. Allman et al. 2005, 2011. It is interesting to note that in all great apes and in postnatal human brains, vents are around 30% or more numerous in the frontoinsular cortex of the right hemisphere compared with their number in the corresponding cortex of the left side. The larger number of vents in the right hemisphere may be related to asymmetry in the central control of the autonomic nervous system, in which the right hemisphere is preferentially involved in sympathetic activation, resulting from negative feedback and subsequent error-correcting behavior. The left hemisphere is preferentially involved in parasympathetic activity associated with reduced tension or calming responses. Thus, it seems that a preferential leftward activation in phi and ACC involve positive and affiliative emotions. This autonomic asymmetry is consistent with the proposal that the right hemisphere responds to the unexpected and the left hemisphere to more routine stimuli. 438 Luigi F. Agnati, Diego G. Dillon, and Kiel F. Uxi. It may therefore be speculated that vent predominance in the right hemisphere in the postnatal period is related to the right hemisphere specialization in humans, at least to the social emotions that are of basic importance for self-consciousness. Allman et al. 2005, 2011. An extension of this line of thinking suggests that the central control of the sympathetic system involves vent and phi, especially in the right hemisphere that is associated with sympathetic autonomic activity. Craig 2005. Thus, the vent predominance in the right hemisphere supports a possible role of these neurons in the aesthetic processing. Actually, aesthetic appreciation always has the kind of arousing nature found associated with the right insula activation. Hence, this brain region may both allow first integration of the visual inputs from the artwork inspection with a feeling of self, see above in Craig 2009. Thereafter, especially by their large, rapidly conducting axons, vents may rapidly relay this information to other parts of the brain and hence play an important role in the assembly of the mosaics of FMS involved in the artwork's production/appreciation. 2.4.1.3 vents as target neurons of VT signals is already mentioned. Important contributions by Insel, Young, and colleagues indicate that the oxytocin and vasopressin V1A receptors mediate social bonding and the rewarding aspects of social bonding. Young et al. 2001, Young et al. 2004, Insel 2010. Allman and collaborators tested adult human ACC and phi tissue for reactivity to antibodies raised against the vasopressin and oxytocin receptors. These authors have demonstrated that antibodies specific for the V1A receptor label a subpopulation of vents, as well as pyramidal neurons in layers 2/3 and 5 of ACC and phi. The pattern of labeling was interesting since apical dendrites labeled with the V1B receptor antibody form columns that span layer 5 to layer 1. Allman et al. 2005, 2011. It has also been shown that vents are strongly labeled with antibodies to 5-HT2B receptor, see below, and to the dopamine D3 receptor, which is a high-affinity dopamine receptor that has been proposed to signal the expectation of reward under uncertainty. Sokoloff and Schwartz 2002. It should be noted that the 5-HT2B receptor, strongly expressed on the vents, is rarely expressed elsewhere in the CNS, see Baumgarten and Goddard 1997, but it is also strongly expressed in the human gut. It has been proposed that serotonin might serve as an antagonistic signal to dopamine, with serotonin signaling punishment and dopamine signaling reward. Et al. 2002. The activation of the 5-HT2B receptor on vents might, therefore, be an opponent to the dopamine D3 signal of reward expectation. Allman 2005. In agreement with these neurochemical findings, activation of phi and ACC increases with the degree of situations in which the subject sustains a gambled loss, punishment, and then switches to a different behavioral strategy, implying that in normal subjects these areas are involved in adaptive decision-making and cognitive flexibility. Carter et al. 2012. As shown in figure 22.2, the several receptors described by Allman and co-workers in vents can be targets for monoamines and neuropeptides working as WT and/or VT signals and contributing to the control of aforementioned behaviors. Art is a human instinct-like behavior 439. It should be noticed that peripheral inputs either by the APNTS and/or the AB3BBH can reach ACC and phi that, see also Allman et al. 2005, play an important role in interoception enhancing conscious awareness of visceral activity. Allman 2005. This could be the neurobiological substrate that gives a somatic component to the aesthetics appreciation. Point 5. This proposal is in agreement with Damasio's theory of somatic states, since he proposed that such monitoring of sensations arising from the body is crucial to adaptive decision-making. Damasio 1995, Ringel et al. 2006. Thus, according to our view, it may be considered that the complexity of aesthetics appreciation can be traced to the depths of human homeostasis, somatic and psychic homeostasis, and both WT and VT, brain-born and peripherally born, play important and complementary roles. As a matter of fact, vasopressin can be, inter alia, also a CSF-VT-mediated signal since, as pointed out recently for oxytocin, Vining et al. 2010, it can reach many brain areas, Suits and Suits 2003. Thus, as suggested by our group in 1986, Agnati et al. 1986, 2010, Agnati and Fuchs 2000, see also the general premise, CSF is used as a broadcasting channel to send coordinated messages, monoamines and peptides, to a wide variety. Figure 22.2 schematic representation of a von Economo neuron, VEN. The main wiring and volume transmission inputs are indicated as well as the main output by the large rapidly conducting axon. Von Economo neuron is a hyperintegrated neuron, integrated input from neurons of the many-column VT signals, integrated output to functional module mosaics of many cortical areas involved in artwork appreciation, large projection axons VT signals, integrated input from neurons of the many-column, integrated input from neurons of the many-column, integrated input from neurons of the many-column VT signals, DA35HT2BV1A 440 Luigi F. Agnati, Diego G. Dillon, and Kiel F. Uxi of nearby and distant brain areas contributing considerably to the VT communication processes affecting mainly but not only periventricular brain areas and deeply affecting behavioral states. As discussed by Nadal and collaborators, Nadal et al. 2008, and pointed out earlier, the seemingly varied results of the neuroimaging studies are compatible with the general model linking aesthetics to the neuroscience of visual and affective processing as well as reward systems in decision-making. Chaturji 2011. Thus, engaging visual properties of paintings increases activity within ventral visual cortices. Aesthetic judgments activate parts of the dorsolateral prefrontal and medial prefrontal cortices. In addition, emotional responses to these stimuli activate orbitofrontal as well as anterior cingulate cortices. Here we have proposed a more complex frame where both the peripheral inputs by the soma, and not only the visual inputs, affect the eudaimonia of the subject and are integrated with the brain-borne signals which are also the results of previous experiences and of the psychic state and susceptibility of the subject. An ugly or even a terrifying painting can activate the peculiar, complex neurochemical machinery of the human brain which, by judging an object as an artwork, can often trigger extraordinary effects on the psychic homeostasis of a sensitive subject. 622.4.2 Possible role of VENS in the functional organization of insula and ACC. Understanding the VENS distinctive relationship to other cortical neuron types as well as comparing VENS in humans versus other mammals could shed light on their neurobiological role in the ACC and in the phi cortex and hence on their contribution to some specific cognitive functions. Among the morphological and functional human differences, Premack, 2007, cites evidence showing that our species has not only many more and larger VENS than apes, but also far wider perimeters of dendrites, an average of 51 in humans compared with 36 in chimpanzees and monkeys. Watson and colleagues, 2006, suggest that VENS are designed to perform relatively simple integrated functions within a cortical column before conveying output to other brain regions for further processing. These findings are highly interesting, but we would like to propose a different view. As already outlined in section 22.4.1.3, we propose that VENS are a special type of hub neurons of FMS and the phi and ACC capable of integrating few but selected WT inputs, mainly from neighboring neurons, and several VT signals, also broadcasted via the CSF channel. Thus, they may carry out an extensive integration that can be rapidly communicated via large VEN axons to several brain areas. Stimpson et al. 2011. This special role of VENS can also be deduced by the cited observation that human VENS are located in only two parts of the human brain, the ACC and the phi cortex, which are involved in socially crucial tasks, such as empathy, feelings of guilt, and embarrassment. In agreement with such a view, neuropathological data demonstrate that the selective destruction of VENS, as in the early stages of frontotemporal dementia, is associated to profound deficits in empathy, social awareness, and self-control. Seeley et al. 2006. Art is a human instinct-like behavior 441.2.4.2.1 Possible role of von Economos neurons in the redeployment of insula and anterior cingulate cortex. Anderson has put forward the interesting proposal of the creative reuse of existing neural components, which may have played a significant role in the evolutionary development of cognition. Thus, Anderson, 2010, analyzes the problem of regional brain specialization under an evolutionary perspective, taking into account the tinkering principle proposed more than 3 decades ago by Jacob, 1977. Jacob claimed that evolution is a process that tinkers, and novelties come from previously unseen associations of already available material. As Anderson points out, over the past several years it has been assessed that, for example, although Broca's area is associated with language processing, it is also involved in many different action and imagery-related tasks. Anderson 2010, Goldrack 2006. There are obvious evolutionary advantages of redeployment of brain areas in Anderson, 2010, analyses this phenomenon in relation with cognition by careful recent meta-analyses of imaging results that support the view that most regions of the brain, even fairly small regions, appear to be activated across diverse task categories. The meta-results also suggest that the brain achieves its variety of functions by putting the same regions together in different patterns of functional cooperation. This view chimes with our proposal of the mosaic assembly of FMS. The tinkering principle suggests that special types of neurons, such as VENS, could have been exaptated with a plastic rebuilding of the circuits allowing peculiar functional reuse of insula and ACC. Taken together, it is proposed that the exaptive functions of ACC and phi in artworks production/appreciation may be the result of a more complex dynamic and plastic reassemblage of FM mosaics, in particular of those having VENS as a hyper-integrative output. It should, however, be noted that such an innovative assemblage of the available material may occur at various miniaturization levels of these FMS. In other words, the tinkering process of VENS-controlled FMS can allow the emergence of novelties that, by VENS projections, rapidly and deeply affect several and also distant brain areas which could be involved in FM mosaics carrying out emergent functions, such as the appreciation of art. 22.5 Conclusion. The main questions posed by this chapter have been 1. Why artworks? 2. Artworks and eudaimonia, psychic vs somatic homeostasis. 22.5.1 Why artworks? An interesting comment is made by Nadal and Pierce, 2011. The first and most basic aspect is to propose theories about how artists might use an implicit understanding of the brain's perceptual systems to engage their audience in their work. According to our hypothesis, the transfer of a complex message by artworks depends on the unique instinct-like communication of human beings. Nadal and Pierce, 2011, continue. The second approach goes beyond such observations to neuropsychological and clinical examinations of how disrupting brain function affects artistic creation and appreciation. Nadal and Pierce suggest that beauty is of little relevance to many manifestations of art, both around the world and throughout history, which may have been created to intimidate, induce sorrow, to broadcast grandeur, to make us reflect on our own existence. Indeed, contemporary Western art includes many instances of works that were explicitly conceived as a reaction against the concept of beauty. Barely 2005. Further, a given artwork often serves a multitude of purposes for different people, in different contexts, at different times. It is, therefore, interesting that Brown and collaborators proposed naturalizing aesthetics, Brown 2011, by observing that human neuroimaging studies have shown convincingly that the brain areas that mediate aesthetic responses to artworks overlap those that mediate the appraisal of objects of evolutionary importance, such as the desirability of food items or the relative attractiveness of potential mates. Hence, it is likely that artworks are appreciated by exaptation of neural systems that evolved to evaluate objects of more primary survival importance. Our proposal, while not discarding this view, takes also into account the human communication processes that, thanks to the abstraction capacity of the human brain and the bipedal conditions with the possibility of using hands to make tools, have been exaptated, leading to the emergence of an instinct-like need to communicate by symbols and to produce artworks, which as Young points out are as necessary to us as food or sex. Furthermore, we suggest that artworks are an artist's attempt to communicate a message present in her inner world that may or may not be derived from an environmental input. Agneta et al. 2007.7 Thus, artworks can convey messages that extend beyond the physical confines of humans in time and space, and the appreciation of art by other human beings is due to the fact that they gain access to these messages. According to our view, the complexity of the human brain has, therefore, allowed the emergence of an instinct-like need to communicate not simply the features of the outer world but also aspects of the subject's inner world. A description of the detachment from the outer world to communicate a message of the inner world is described in a famous novel by Bernhard. 9 The current hypothesis may also suggest a possible original point of view on recent artworks that break with the previous art tradition. These pop artworks, indeed, do not appear to look for an ideal beauty or want to communicate a message about some complex intellectual aspect of the artist's inner world. Rather, they seem to represent a crude denouncement of some invasion by the mass media of the inner world of the human beings. This view could be grasped by comparing, for example, an artwork conveying mainly a message of the inner world of an artist with an artwork, in particular pop art products, conveying mainly a message anchored to the modern outer world. The comparison may suggest a colonization of the inner world by the outer world occurs, likely thanks to mass media. Chapter 23 Neurobiological Foundations of Art and Aesthetics Edmund G. Rolls 23.1 Introduction A theory of the neurobiological foundations of aesthetics and art is described. This has its roots in emotion, in which what is pleasant or unpleasant, a reward or punisher, is the result of an evolutionary process in which genes define the pleasant or unpleasant goals for action. Rolls 2005, 2014. It is argued that combinations of multiple such factors provide part of the basis for aesthetics. To this is added the operation of the reasoning syntactic brain system which evolved to help solve difficult multi-step problems, and the use of which is encouraged by pleasant feelings when elegant, simple, and hence aesthetic solutions are found that are advantageous because they are parsimonious, and follow Occam's razor. The combination of these two systems, and the interactions between them provide an approach to understanding aesthetics that is rooted in evolution and its effects on brain design and function. Roles 20118, 2012. I start by considering how effective value is generated in the brain as a solution to the problem of how genes can specify useful goals for actions. This is more efficient and produces more flexible behavior than by specifying the actions themselves. Then, in sections 23.5 and 23.6, I develop this theory further into a theory of the foundations of aesthetics and art. 23.2 Emotions as states elicited by rewards and punishers. Emotions can usefully be defined, operationally, as states elicited by rewards and punishers that have particular functions. Roles 1999, 2005, 2014. The functions are defined below and include working to obtain or avoid the rewards and punishers. A reward is anything for which an animal, which includes humans, will work. A punisher is anything that an animal will escape from or avoid. A diagram summarizing some of the emotions associated with the delivery of a particular reward or punisher or a stimulus associated with them, or with the omission of a reward or punishment, is shown in figure 23.1. It is emphasized that this shows states elicited by any one reward or punisher, and that there are many different rewards and punishers. This helps to account for many different emotions. Roles 1999, 2005, 2014. 454 Edmund T. Rolls. The proposal that emotions can be usefully seen as states produced by instrumental reinforcing stimuli follows earlier work by Melanson, 1967, Weiss-Krauss, 1968, Gray, 1975, 1987, and Rolls, 1986A, 1986B, 1990, 1999, 2000, 2005. Instrumental reinforcers are stimuli which, if their occurrence, termination, or omission is made contingent upon the making of a response, action, alter the probability of the future emission of that response. Some stimuli are unlearned reinforcers, e.g. the taste of food if the animal is hungry, or pain, while others may become reinforced by learning because of their association with such primary reinforcers, thereby becoming secondary reinforcers. This foundation has been developed. See Rolls 1986A, 1986B, 1990, 1999, 2000, 2005, 2014, to show how a very wide range of emotions can be accounted for, as a result of the operation of a number of factors, including the following. 1. The reinforcement contingency, e.g. whether reward or punishment is given, or withheld. See figure 23.1. Figure 23.1. Some of the emotions associated with different reinforcement contingencies are indicated. Intensity increases away from the center of the diagram, on a continuous scale. The classification scheme created by the different reinforcement contingencies consists of 1. The presentation of a positive reinforcer, S+, 2. The presentation of a negative reinforcer, S, 3. The omission of a positive reinforcer, S+, or the termination of a positive reinforcer, S+, and 4. The omission of a negative reinforcer, S, or the termination of a negative reinforcer, S. Ecstasy, S, and elation, pleasure, relief, S, and or S, and I, S, or S, I, apprehension, grief, rage, anger, frustration, sadness, fear, terror, S, neurobiological foundations of art and aesthetics. 455. 2. The intensity of the reinforcer, see figure 23.1. 3. Any environmental stimulus might have a number of different reinforcement associations, e.g. a stimulus might be associated both with the presentation of a reward and a punisher, allowing states such as conflict and guilt to arise. 4. Emotions elicited by stimuli associated with different primary reinforcers will be different. A list of some primary reinforcers to illustrate some of the different affective states is provided in Emotion and Decision Making Explained, Rolls 2014, and in Neuroculture, Rolls 2012. 5. Emotions elicited by different secondary reinforcing stimuli will be different from each other, even if the primary reinforcer is similar. 6. The emotion elicited can depend on whether an active or passive behavioral response is possible. For example, if an active behavioral response can occur to the omission of a positive reinforcer, then anger might be produced, but if only passive behavior is possible, then sadness, depression, or grief might occur. By combining these 6 factors, it is possible to account for a very wide range of emotions. For elaboration, see Rolls 2014. 23.3 The functions of emotion. The most important functions can be summarized as follows. Rolls 1990, 1999, 2005, 2014. 1. The elicitation of autonomic responses, e.g. a change in heart rate, and endocrine responses, e.g. the release of adrenaline. These prepare the body for action. 2. Flexibility of behavioral responses to reinforcing stimuli. Emotional and motivational states allow a simple interface between sensory inputs and action systems. The essence of this idea is that goals for behavior are specified by reward and punishment evaluation. When an environmental stimulus has been decoded as a primary reward or punishment, or, after previous stimulus reinforcer association learning, a secondary rewarding or punishing stimulus, then it becomes a goal for action. The person can then perform any action, instrumental response, to obtain the reward, or to avoid the punisher. Thus there is flexibility of action. The emotional state intervenes between delivery of the stimulus and its decoding as rewarding or punishing, which produces the emotional state, and the learning and performance of the action, which may only be possible with some delay. In this sense, for goal-directed action an intervening state is required. For overlearned stimulus response habit-based responses, no intervening state is necessary, and emotional states need not be present. This is one of the reasons why I propose that emotions are part of a brain/behavior system in which arbitrary actions must be learned to reinforcing stimuli in order to obtain goals. This is an important reason why I relate emotions to the evolution of instrumental actions to rewarding and punishing stimuli, as intervening states are needed in 456 Edmund T. Rolls. This process, Rolls 2014. The motivation that is part of the intervening state is to obtain the reward or avoid the punisher, and animals must be built to obtain certain rewards and avoid certain punishers. Further, and very importantly, for this shows why emotions have evolved, primary or unlearned rewards and punishers are specified by genes which effectively specify the goals for action. This is the solution which natural selection has found for how genes can influence behavior to promote their fitness, as measured by reproductive success, and for how the brain could interface with sensory systems to action systems, and it is an important part of Rolls' theory of emotion. 1990, 1999, 2005, 2014. Selecting between available rewards with their associated costs, and avoiding punishers with their associated costs, is a process that can take place both implicitly, unconsciously, and explicitly using a language system to enable long-term plans to be made. Rolls 2005, 2008. These many different brain systems, some involving implicit evaluation of rewards, and others explicit, verbal conscious evaluation of rewards and planned long-term goals, must all enter into the selector of behavior. See figure 23.2. This selector is poorly understood, but it might include a process of competition between all the competing calls: language cortex, association cortex, secondary cortex, primary cortex, input, primary reinforcers, e.g. taste, touch, pain, amygdala, and orbitofrontal cortex, cortical motor and planning areas, explicit actions, brainstem, spinal cord, ventral striatum, alamus striatum, cingulate cortex, premotor cortex, etc. Implicit actions, learned autonomic responses, reacts, figure 23.2. Dual routes to the initiation of action in response to rewarding and punishing stimuli. The inputs from different sensory systems to brain structures such as the orbitofrontal cortex and amygdala allow these brain structures to evaluate the reward or punishment related value of incoming stimuli, or of remembered stimuli. The different sensory inputs enable evaluations within the orbitofrontal cortex and amygdala based mainly on the primary, unlearned, reinforcement value for taste, touch, and olfactory stimuli, and on the secondary, learned, reinforcement value for visual and auditory stimuli. In the case of vision, the association cortex, which outputs representations of objects to the amygdala and orbitofrontal cortex, is the inferior temporal visual cortex. One route for the outputs from these evaluated brain structures is via projections directly to structures such as the basal ganglia, including the striatum and ventral striatum, to enable implicit, direct behavioral responses based on the reward or punishment related evaluation of the stimuli to be made. The second route is via the language systems of the brain, which allow explicit decisions involving multi-step syntactic planning to be implemented. Neurobiological foundations of art and aesthetics. 457 on output, and might involve the anterior cingulate cortex and basal ganglia in the brain. Rolls 2005, 2008, 2014. See figure 23.2. 23.4 Dual routes to action, gene-defined goals, and syntactic reasoning. The first route is via the brain systems that have been present in non-human primates such as monkeys, and to some extent in other mammals, for millions of years, and have built in the brain a system for defining these goals. Achieving these goals feels pleasant or unpleasant. The goals may be primary reinforcers, or stimuli associated with them by learning. The second route in humans and also perhaps closely related animals involves a computation with many if-then statements to implement a plan to obtain a reward. In this case, the reward may actually be deferred as part of the plan, which might involve working first to obtain one reward, and only then to work for a second more highly valued reward, if this was thought to be overall an optimal strategy in terms of resource usage, e.g. time. In this case, syntax is required, because the many symbols, e.g. names of people, that are part of the plan must be correctly linked or bound. Such linking might be of the form, if A does this, then B is likely to do this, and this will cause C to do this. The requirement of syntax for this type of planning implies that an output to language systems in the brain is required for this type of planning. See figure 23.2. Thus the explicit language system in humans may allow working for deferred rewards by enabling use of a one-off, individual, plan appropriate for each situation. The question then arises of how decisions are made in animals such as humans that have both the implicit, direct, reward-based instrumental action, and the explicit, rational, planning systems. See figure 23.2, Roles 2008, 2014. One particular situation in which the first, implicit, system may be especially important is when the interests of the genes are being maintained. In contrast, when the implicit system continually makes errors, it would then be beneficial for the organism to switch from automatic, direct action based on obtaining what the orbitofrontal cortex system decodes as being the most positively reinforcing choice currently available, to the explicit conscious control system that can evaluate with its long-term planning algorithms what action should be performed next. The second route to action allows, by reasoning, decisions to be taken that might not be in the interests of the genes, might be longer-term decisions, and might be in the interests of the individual. Thus we may speak of the choice as sometimes being between the selfish genes, Dawkins 1989, and the selfish Venice, Roles 2011b, 2012, 2013a. 23.5a Theory of the Neurobiological Foundations of Aesthetics and Art 23.5.1 Introduction to an outline of the theory. Now that we have a fundamental, Darwinian approach to the value of people, objects, relationships, etc., I propose that this provides a fundamental neurobiological approach to understanding aesthetics and art. I propose that while the gene-specified rewards in 458 Edmund T. Rolls punishers define many things that have aesthetic value, the value that we place on items is enhanced by the reasoning, rational system which enables what produces aesthetic value to become highly intellectualized, as in music. I emphasize at the outset that this does not at all reduce aesthetics to a common denominator. Genetic variation is essential to evolution by natural selection, and this is one reason why we should expect different people to assign aesthetic value differently. But rational thought, which will lead in different directions in different people, partly because of noise caused by random neuronal firing times in the brain, Rolls and Deco 2010, Rolls 2014, and because of what they have learned from the environment, and because different brain areas will be emphasized in different people, will also be different between individuals, so that the rational system will also contribute to differences between individuals in what is considered aesthetic. Indeed, although the theory presented here on the origin of aesthetics is a reductive explanation in that it treats the underlying basis and causes, it should not be seen to reduce aesthetics. Far from it. When we understand the underlying origins and basis of aesthetics, we see that the processes involved are elegant and beautiful, as part of the Darwinian theory. But the approach also provides important pointers about how to enhance aesthetics. For example, by understanding that verbal-level cognitive factors that can be produced by reasoning have a top-down modulatory influence on the first cortical area where value, reward, is made explicit in the representation, the orbitofrontal cortex, Del Raggio et al. 2005, Gravenhorst et al. 2008, and KBT et al. 2008, Rolls 2013b 2014, we can see ways in which we can enhance our aesthetic feelings. For example, if love be the thing, then it can be heightened by explicitly choosing the musical treatment of it in Wagner's Tristan and Isolde. I should also emphasize that aesthetic value judgments will usually be influenced by a number of different value factors, so that while accounting for an aesthetic judgment by just one of the value factors I described as will often seem too simple, it does seem that aesthetic value judgments can be understood by combinations of some of the factors I described. I emphasize that rewards contribute to what makes stimuli or brain processing positively aesthetic, beautiful, and that the punishers contribute to what makes stimuli or processing in the brain aesthetically negative, lacking beauty, ugly, or distasteful. Both rewards and punishers are needed for the theory of aesthetics. The overall theory of the origin of aesthetics I propose is that natural selection, whether operating by survival or adaptation selection, or by sexual selection, operates by specifying goals for action, and these goals are aesthetically and subjectively attractive or beautiful, Rolls 2005, 2014, or the opposite, and provide what I argue here is the origin of many judgments of what is aesthetic. 23.5.2 Survival or adaptation selection. Natural selection in a narrow sense. Natural selection encompasses in its broad sense both survival or adaptation selection, and sexual selection. Both are processes now understood to be driven by the selection of neurobiological foundations of art and aesthetics 459 genes, and it is gene competition and replication into the next generation that is the driving force of biological evolution. Dawkins 1986, 1989. The distinction can be made that with survival or adaptation selection, the genes are selected to make the individual stronger, healthier, and more likely to survive and reproduce, whereas sexual selection operates by sexual choice, selecting for genes that may or may not have survival value to the individual but enable that individual to be selected as a mate or to compete for a mate in intersexual selection and thus pass on the genes selected by intersexual or intersexual selection to the offspring. More generally, we might have other types of selection as further types of natural selection, including selection for good parental care, and kin selection. Many of the reward and punishment systems described by Rolls, 2014, deal with reward and punishment decoding that has evolved to enable genes to influence behavior in directions in a high-dimensional space of rewards and punishments that are adaptive for survival and health of the individual, and thus promote reproductive success or fitness of the genes that build such adaptive functionality. We can include kin-related altruistic behaviors because the behavior is adaptive in promoting the survival of kin, and thus promoting the likelihood that the kin, who contain one's genes, and are likely to share the genes for kin altruism, survive and reproduce. We can also include reciprocal altruism as an example of survival or adaptation selection. Tribalism can be treated similarly, for it probably has its origins in altruism. Resources and wealth are also understood at least in part as being selected by survival natural selection, in that resources and wealth may enable the individual to survive better. As we will see next, resources and wealth can also be attractive as a result of sexual selection. 23.5.3 Sexual selection. Darwin, 1871, also recognized that evolution can occur by sexual selection, when what is being selected for is attractive to potential mates. Intersexual selection, for example the peacock's tail, and a slim, young-looking physique in females as a signal of fertility, or helps in competing with others of the same sex. Intersexual selection, e.g. the deer's large antlers, and a strong male physique. Overall, Darwinian natural or survival selection increases health, strength, and potentially resources, and survival of the individual, and thus ability to mate and reproduce, and to look handsome or beautiful. Intersexual sexual selection does not make the individual healthier, but does make the individual more attractive as a mate, as in female choice, an example of intersexual selection. Intrasexual sexual selection does not necessarily help survival of the individual, but does help in competition for a mate, for example in intimidation of one male by another. Darwin 1871, Kapler and Van Schaik 2004. The differences between survival and sexual selection are elaborated elsewhere. Rolls 2011a, 2012, 2014. 23.5.4 Beauty in men and women. Given this background in the processes that drive evolution to make certain stimuli and types of brain processing rewarding or punishing, in this section I examine how the 460 Edmund T. Rolls contribute to what factors make men and women aesthetically beautiful, and that influence their depiction in art. 23.5.4.1 Female preferences. Factors that make men attractive. Factors that across a range of species influence female selection of male mates include the following. 23.5.4.1.1 Athleticism. This is the ability to compete well in mate selection, including being healthy and strong, as this will be useful for her genes when present in her male offspring. Consistently, women show a strong preference for tall, strong, athletic men. Buss and Schmidt 1993. 23.5.4.1.2 Resources, power, and wealth in species with shared parental investment, which include many birds and humans. Having power and wealth may be attractive to the female, because they are indicators of resources that may be provided for her young. Consistently, women place a greater premium on income or financial prospects than men. Buss 1989, 2008. 23.5.4.1.3 Status correlates with the control of resources, e.g. alpha male chimpanzees take precedence in feeding, and therefore acts as a good cue for women. Women should therefore find men of high status attractive, e.g. rock stars, politicians, and tribal rulers, and these men should be able to attract the most attractive partners. Consistent with this, cross-culturally, women regard high social status as more valuable than do men, and attractive women often marry men of high status. Buss 1989, 2008. Status may be attractive because of direct effects, e.g. as an indicator of resources for children, or because of indirect effects, because high status implies good genes for offspring. 23.5.4.1.4 Age status and higher income are generally only achieved with age, and therefore women should generally find older men attractive. Cross-culturally, women prefer older men, 3.42 years older on average, and marriage records from 27 countries show that the average age difference was 2.99 years. Buss 1989. 23.5.4.1.5 Ambition and industriousness. These may be good predictors of future occupational status and income and are attractive to women. Buss 1989. 23.5.4.1.6 Testosterone-dependent features. These may also be attractive. These features include a strong, longer and broader jaw, a broad chin, strong cheekbones, defined eyebrow ridges, a forward central face, and a lengthened lower face. Secondary sexual characteristics that are a result of pubertal hormone levels. 23.5.4.1.7 Symmetry. This may be attractive in both males and females, in that it may reflect good development in utero, a non-harmful birth, adequate nutrition, and lack of disease and parasitic infections. Thornhill and Gangestad 1999. 23.5.4.1.8 Dependability and faithfulness. These may be attractive, particularly where there is paternal investment in bringing up the young, as these characteristics may indicate stability of resources. Buss ETAL 1989. Neurobiological foundations of art and aesthetics 461 23.5.4.1.9 Risk taking by men. This may be attractive to women, perhaps because it is a form of competitive advertising. Surviving the risk may be an honest indicator of high-quality genes. Barrett ETAL 2002. 23.5.4.1.10 Other characteristics that may not be adaptive in terms of the survival of the male, but that may be attractive because of intersexual sexual selection, are common in birds, perhaps less common in most mammals, though present in some primates. Kapler and Van Schaik 2004, and may be present in humans. See section 23.5.3. 23.5.4.1.11 Odor. The preference by women for the odor of symmetrical men is correlated with the probability of fertility of women as influenced by their cycle. Gangestad and Simpson 2000. Another way in which odor can influence preference is by pheromones that are related to major histocompatibility complex, MHC, genes, which may provide a molecular mechanism for producing genetic diversity by influencing those who are considered attractive as mates. Rolls 20118, 2012, 2014. 23.5.4.2 Male preferences. What makes women attractive and beautiful to men. Males are not always indiscriminate. When a male chooses to invest, e.g. to produce offspring, there are preferences for the partner with whom he will make the investment. Accurate evaluation of female quality, reproductive value, is therefore important, and males look out for cues to this, and find these cues attractive, beautiful, and rewarding. The factors that influence attractiveness include the following. Barrett ETAL 2002, Rolls 20118, 2012, 2014. 23.5.4.2.1 Youth is fertility and reproductive value in females is linked to age. Reproductive value is higher when younger, and actual fertility in humans peaks in the 20s. Males, unlike females, place a special premium on youth. It is not youth per se that men find attractive, but indicators of youth. For example, Neotenous traits such as blonde hair and white eyes. An example of this preference is that male college students preferred an age difference on average of 2.5 years younger. Buss 1989. Another indicator of youth might be a small body frame, and it is interesting that this might contribute to the small body frame of some women in this example of sexual dimorphism. 23.5.4.2.2 Beautiful features. Features that are most commonly described as the most attractive tend to be those that are estrogen dependent. For example, full lips and cheeks, and short lower facial features. Estrogen caps the growth of certain facial bones. Why do women apparently compete for men by paying attention to their own beauty and fashion? Perhaps the answer that males who are willing to make major investments of time and resources in raising the children of a partner are a somewhat limiting resource, as other factors may make it advantageous genetically for men not to invest all their resources in one partner, and because women are competing to obtain and maintain this scarce resource. Faithful men may be a limited resource because there are alternative strategies that may have a low cost, whereas women are essentially committed to a considerable investment in their offspring. 462 Edmund T. Rolls. Given that men are a scarce resource, and that women make such a major investment in their offspring that they must be sure of a man's commitment to invest before they commit in any way, we have a scientific basis for understanding why women are reserved and more cautious and shy in their interactions with men, which has been noticed to be prevalent in visual art, in which men look at women, but less vice versa. Berger 1972. 23.5.4.2.3 Body fat. The face is not the only cue to a woman's reproductive capacity, her attractiveness, and beauty. Although the ideal body weight varies significantly with culture, in cultures with scarcity, obesity is attractive and relates to status, a trend evident in beautiful painting throughout its history. The ideal distribution of body fat seems to be a universal standard, as measured by the waist-to-hip ratio, which cancels out effects of actual body weight. Consistently, across cultures, men preferred an average ratio of 0.7, small waist/bigger hips, when rating female figures, line drawings and photographic images, for attractiveness. Singh and Lewis 1995. At a simpler level, a low waist-to-hip ratio is an indication that a woman is not already pregnant, and is thus a contributor to attractiveness and beauty. 23.5.4.2.4 Fidelity. The desire for fidelity in females is most obviously related to concealed ovulation. See the following in emotion and decision-making explained. Rolls 2014, and therefore the degree of paternity uncertainty that males may suffer. 23.5.4.2.5 Attractiveness in the time of ovulation. Although ovulation in some primates and in humans is concealed, it would be at a premium for men to pick up cues to ovulation and find women highly desirable and beautiful at this time. Possible cues include an increased body temperature reflected in the warm glow of vascularized skin, Vandenberg and Frost 1986, and pheromonal cues. Another possibly unconscious influence might be on the use of cosmetics and the types of clothes worn, which may be different close to the time of ovulation. In humans, male investment in caring for the offspring means that male choice has a strong effect on intersexual selection in women. Female cosmetic use and designer clothing could be seen as weapons in this competition, and perhaps are reflected in extreme female self-grooming behaviors such as cosmetic surgery, or pathological disorders such as anorexia, bulimia, and body dysmorphic disorder. By bombarding people with images of beautiful women, the media may heighten intersexual selection even further, pushing women's competitive mating mechanisms to a major scale. 3.5.5 Pair bonding, love, and a beautiful partner attachment to a particular partner by pair bonding in a monogamous relationship, which in humans becomes manifest in love between pair bonded parents, and which occurs in humans in relation to the advantage to the man of investing in his offspring, may have special mechanisms to facilitate it. One is oxytocin, a hormone released from the posterior pituitary, whose other actions include the milk letdown response, which is released during mating and which promotes attachment, making a partner attractive. Lee et al. 2009. Neurobiological foundations of art and aesthetics 463 are similar mechanisms at work in humans to promote pair bonding and love, and what is found to be aesthetically attractive, and to influence depictions in art. There is as yet no definitive evidence for this, but in humans, oxytocin is released by intercourse, and especially at the time of orgasm, in both women and men. Meston and Froelich 2000, Kruger et al. 2003. 3.5.6 Parental attachment. Beautiful children. Many mammal females make strong attachments to their own offspring, and this is also facilitated in many species by oxytocin. In humans, oxytocin is released during natural childbirth, and rapid placing of the baby to breastfeed and release more oxytocin, of Ms. Maubert 1998, might further facilitate maternal attachment to her baby. Prolactin, the female hormone that promotes milk production, may also influence maternal attachment and how beautiful a mother thinks her child is. It is certainly a major factor in humans that bonding can change quite suddenly at the time that a child is born, with women having a strong tendency to shift their interests markedly towards the baby as soon as it is born, probably in part due to hormonal influences, and this can result in relatively less attachment behavior to the husband. The tendency to find babies beautiful is not of course restricted to parents of their own children. Part of the reason for this is that in the societies in which our genes evolved with relatively small groups, babies encountered might often be genetically related, and the tendency to find babies beautiful is probably a way to increase the success of selfish genes. One may still make these aesthetic judgments of babies in distant countries with no close genetic relationship, but this does not of course mean that such judgments do not have their evolutionary origin in kin-related advantageous behavior. 3.5.7 Synthesis on beauty. In humans we see that many factors are involved in making humans attractive and beautiful. All may contribute to different extents, and differently in different individuals, and moreover we may not be conscious of some of the origins of our aesthetic judgments but may confabulate reasons for what we judge to be aesthetic. When there is a biological foundation for art, for example when it is figurative, and especially when it is about human figures, there may be a basis for consensus about what is good art that stimulates our rational system and at the same time speaks to what we find beautiful due to our evolutionary history. However, if art becomes totally abstract, we lack the biological foundation for judging whether it is aesthetically beautiful, and judgments may be much more arbitrary and driven by short-term fashion. Some abstraction away from very realistic and figurative in art can of course have advantages because it allows the viewer to create in his or her own experience of a work of art by adding his or her own interpretation of it. There is an important point here about the separation between art and the world. Objects of art can idealize beauty, and enhance it. An example is the emphasis on thin bodies, long limbs, and athletic poses found in some Art Deco sculpture, for example in the works 464 Edmund T. Rolls of Lawrence Here what is beautiful can be made supernormal, one might say in the literal sense supernatural. Another example is in the emotion in the music of Wagner's Tristan and Isolde. We see that art can emphasize and thus idealize some of the properties of the real world, and lose other details that do not enhance, or distract from it. This abstraction of what we find beautiful due to evolution can be seen in some semi-figurative/semi-abstract art, as in some of the line drawings of humans by Matisse and Picasso. It is also found in the sculptures of human forms of Brancusi. What I argue is that if art becomes too abstract then it loses the aesthetic value that can be contributed by tapping into these evolutionary origins. Interesting cases are found in the sculptures of Barbara Hepworth and Henry Moore. In the case of Barbara Hepworth, I find it interesting that she often retains sufficient figurative allusions in her sculpture to tap into evolutionary origins, and that some of her sculptures do seem to have some relation to male and female forms and relations. Much of the sculpture of Henry Moore is clearly figurative, and where it becomes apparently very abstract it may lose what is gained by tapping into evolutionary origins, but may gain by association and interpretation in relation to his more figurative work. Where art becomes very abstract, as in some of the work of Mark Rothko, perhaps those especially interested are those who have expertise themselves in what is being achieved technically, such as the painting of colors by Rothko. 3.5.8 Sexual selection of mental ability, survival, or adaptation selection of mental ability, and the origin of aesthetics. Miller, 2001, has developed the hypothesis that courtship provides an opportunity for sexual selection to select non-sexual mental characteristics such as kindness, humor, the ability to tell stories, creativity, art, and even language. He postulates that these are courtship tools, evolved to attract and entertain sexual partners. Miller, 2001, also suggests that art, language, and creativity can be explained by sexual selection, and that they are difficult to account for by survival selection. He suggests that art develops from courtship ornamentation, and uses bowerbirds as an evolutionary example. Male bowerbirds ornament their often enormous and structurally elaborate nests or bowers with mosses, ferns, shells, berries, and bark to attract female bowerbirds. The nests are used just to attract females, and after insemination the females go off and build their own cup-shaped nests, lay their eggs, and raise their offspring by themselves with no male support. In this sense, the bowers are useless ornamentations that do not have survival value. Darwin, 1871, himself viewed human ornamentation and clothing as outcomes of sexual selection. Sexual selection for artistic ability does not mean of course that the art itself needs to be about sex. This example helps to show that sexual selection can lead to changes in what is valued and found attractive in areas that might be precursors to art in humans. In Miller's 2001 view, the fine arts are just the most recent and pretentious manifestations of a universal human instinct for visual self-ornamentation, which in turn is a manifestation of sexual selection's universal tendency to ornament individuals with visual advertisements of their fitness. Thus, the human capacity for visual artistry is viewed as a fitness indicator, evolved like the peacock's tail in the bowerbird's bower. Neurobiological foundations of art and aesthetics 465 for a courtship function. So although inherently useless, the bower or work of art is seen as attractive because it is difficult to produce, and might only be made by a brain that is very competent in general, and thus the bower or work of art may act as a fitness indicator. The useful point, Miller 2001, is that although artworks are now commodified and distributed widely so that we may not necessarily know the artist producing the ornament, when we seek the evolutionary origins of art we should remember that any artwork our prehistoric ancestors would have been able to see would have probably been made by a living individual with whom they could have interacted socially or sexually. The artist was never far from his or her work, or else the work could not have functioned as the artist's extended phenotype. Miller, 2000, further suggests that language and creativity may be related to systems that can explore random new ideas, and they also may be courtship devices in males to attract females. My view, elaborated here and elsewhere, Rolls 2008, Rolls and Deco 2010, Rolls 2012, 2014, is that language and creativity have functions that have survival value and thus are not just sexually selected. Indeed, a criticism of the approach of Miller, 2000, is that many of these characteristics, e.g. language, creative solutions, originality, problem solving, may have survival value, and are not purely or primarily sexually selected. For example, syntax and language have many uses in problem solving, planning ahead, and correcting multi-step plans that are likely to be very important to enable immediate rewards to be deferred, and longer-term goals to be achieved. Pinker and Bloom 1992, Rolls 2008, 2012, 2014. In relation to aesthetics, I argue that when syntax is used successfully to solve a difficult problem we feel aesthetic pleasure, and I argue that the generation of pleasure generated by the survival value of good ideas contributes to the appeal of those ideas, and that sexual selection of the ideas as mental ornaments is not the only process at work in aesthetics. Moreover, the notion, Miller 2000, 2001, that art has to do with useless ornaments, useless in the sense that sexual selection is for characteristics that may not have survival value, but may be attractive because they are indicators of fitness, does not have much to say about the utilitarian arts such as simplicity of design and architecture. structure. Perhaps this structure of a piece of music can appeal and be pleasing because it taps into our syntactic system that finds that elegant and simple solutions to problem solving produce pleasure. Further, interest in social relations and knowledge about them is adaptive as it may help to understand who is doing what to whom, and more generally help to understand what can happen to people. A great deal of literary fiction addresses these issues and is not primarily ornamental and without inherent value. Thus, although Miller, 2001, may well be right that there are aspects of art that may be primarily ornamental and useless and these are simply indicators of general mental fitness, though attractive to members of the opposite sex in courtship, I suggest that much art has its roots in goals that have been specified as pleasurable or unpleasurable because of their adaptive or survival value, whether as primary reinforcers, other stimuli associated by learning with these, or rewards of a more cognitive origin that accrue when difficult cognitive, syntactic problems are solved. Rolls 20118, 2012, 2014. 466 Edmund T. Rolls Miller might predict that men should be specialized to have artistic creativity, to provide an ornament that women might find attractive because it is a fitness indicator. Evidence on this is difficult to evaluate, because there have been fewer opportunities available for women in the past, as argued for so beautifully by Virginia Woolf in A Room of One's Own, 1929, and I come to no conclusions, but have the following thoughts. Whereas Virginia Woolf argues about circumstances, one can consider in addition the possibility that women's and men's brains have been subject to different selective pressure in evolution, and that this might contribute to differences in the ways in which they are creative. In terms of artists, composers of music, poets, writers of drama and non-fiction, there appears to be on average a preponderance of men relative to women. This is on average, and there are individual women who, given the distribution around the average, are undoubtedly highly creative in these areas, and have made enormous contributions. If this is the case, and it might take a long time into the future to know, given the imbalance of opportunity in the past, does this mean that sexual selection is the underlying process? I suggest that this would not necessarily be the case. Such a sexual dimorphism could occur by natural adaptation, selection, not by sexual selection, and that women might have specialized for an environmental niche to emphasize child rearing, cultivation including food gathering and preparation, fashioning of clothing, and creating peaceful order among siblings and parents. On the other hand, men might have specialized for an environmental niche to emphasize spatial problem solving, useful for producing and using tools, building shelters, creating structures, etc., and navigational problem solving useful for hunting, all of which would be good for survival. Interestingly, the same, narrow, natural selection pressure might have provided a survival advantage for men to have a stronger physique which is likely to be advantageous when manufacturing items useful for survival such as shelters. Thus interestingly, one of the predictions of sexual selection, sexual dimorphism, including human mental problem solving as well as physique, could in this case have its origin at least partly in adaptation and survival. There is however a possible exception to the generalization that at least in the past men have been more likely to be creative in art than women, and this is the area of literary fiction, where there are many women with high reputations as novelists, e.g. Jane Austen, George Eliot, Virginia Woolf. If women take more to this area of creative art, might this be because of the adaptive value of gossip to women, so knowing about who is doing what to whom, and having an interest and expertise in this, could be adaptive, perhaps helping a woman, and her children, to survive better. Dunbar 1996. If this were the case, there might even be a prediction that women might be relatively better, on average, in areas of fiction, such as novels, where this interest and expertise in mind reading and gossip, might be especially engaged. More generally, the evolutionary survival value approach might argue that women have adapted to relational, social, caring, problem solving, and the novel, particularly the novel of manners, is ideally suited to displaying this specialization. Indeed, the specialization for a caring role is consonant with Carol Gilligan's argument in A Different Voice, 1982, that women's sense of morality concerns itself with the activity of care, responsibility, and relationships. Neurobiological Foundations of Art and Aesthetics 467. The overall point I make is that natural selection, sometimes operating by survival or adaptation selection, and sometimes by sexual selection, and sometimes both, operates by specifying goals for action, and these goals are aesthetically and subjectively attractive or beautiful. Rolls 2012, 2014, or the opposite, and provide what I argue here is the origin of many judgments of what is aesthetic. Many examples of these rewards and punishers, many of which operate for survival or adaptation selection, and many of which contribute to aesthetic experience and judgments, are described elsewhere. Rolls 20118, 2012, 2014. 23.5.9 Fashion and memes. We have seen that sexual selection can provide runaway selective pressure for what is not something that is produced by survival or adaptation selection. In a sense, a fashion, or useless ornament, which may indicate fitness, can be selected for genetically. However, fashion is a strong characteristic of many human aesthetic judgments, and we may ask if there are further reasons for this that are not to do with genetic variation, which necessarily takes place over generations, but that instead operate over timescales of months to years. Such fashions, in, for example, clothing, may occur because they fit adaptations of the human mind, themselves the result of adaptive pressure in evolutionary history. For example, the human mind will be attracted towards new ideas, of clear adaptive value, for it is only by exploring new ideas that advantage may be gained partly as a result of finding a match with one's own genetically influenced capacities. Rolls 2014. In this way, there may be runaway changes that do not necessarily make the individual better adapted to the environment. Of course, many factors, again frequently of evolutionary origin, influence fashion, including its cost, of which the brand is an indicator, which helps to make it attractive as it indicates wealth, plentiful resources, and status, and the elegance and simplicity of the idea, which is argued below. The human mind finds attractive because simplicity often is a good indicator of a correct and useful solution to a problem. It is argued that means, Blackmore 1999, ideas that follow some of the rules of fashion, fit these properties of the human mind. 23.5.10 The elegance and beauty of ideas, and solving problems in the reasoning system. Solving difficult problems feels good, and we often speak about elegant and beautiful solutions. What is the origin of the pleasure we obtain from elegant ideas? What makes them aesthetically pleasing? It is suggested that solving problems should feel good to us, to make us keep trying, because being able to solve difficult problems that require syntactic operations may have survival value. Rolls 2014. But what is it that makes simple ideas and solutions, those with fewest premises, fewest steps to the solution, and fewest exceptions for a given level of complexity of the problem, particularly aesthetically pleasing, so much so that physicists may use this as a guide to their thinking? It is suggested that the human brain has become adapted to find simple solutions aesthetically pleasing because they are more likely to be correct. Rolls 2012, 2014, and this is exactly the thrust of parsimony in Occam's razor, the principle of heuristic that entities and hypotheses should not 468 Edmund T. Rolls be multiplied needlessly. The simplest of two competing and otherwise equally effective theories is to be preferred. The principle states that the explanation of any phenomenon should make as few assumptions as possible, eliminating those that make no difference in the observable predictions of the explanation or theory. This finds expression in art, in, for example, the structure of a piece of music, in the solution of how to incorporate perspective into painting, which developed over hundreds of years and was helped by the camera obscura, and in the interest by Vitruvius and Leonardo in the proportions of the human body, tapping into our gene-based appreciation of that, to provide rules for proportions in architecture. Of course, focus on intellectual aspects of art can lead to art that we may find fascinating and revealing, if not conventionally physically beautiful, as in some of the work of Francis Bacon's. Factors such as cultural heritage and familiarity with the rules of a system can also make a style of architecture more appealing than something very unfamiliar. Some of the history of ecclesiastical architecture in England from the 11th to the 15th century, from Norman through early English and decorated to perpendicular styles, can also be seen as solutions to difficult architectural problems, of how to increase the light and feeling of space in a building, and how to create an impression of grand and daring height. 3.5.11 Cognition and aesthetics. Not only can operation of our reasoning, syntactic, explicit, system lead to pleasure and aesthetic value, as just described, but also this cognitive system can modulate activity in the emotional, implicit, gene-identified goal system. This cognitive modulation, working from the level of word descriptions, can have modulatory effects right down into the first cortical area, the orbitofrontal cortex, where affective value, including aesthetic value such as the beauty found in a face, is first made explicit in the representation. O'Doherty et al. 2003, Del Raggio et al. 2005, Gravenhorst et al. 2008, McCabe et al. 2008, Rolls and Gravenhorst 2008, Gravenhorst and Rolls 2011, Rolls 2012, 2014. Indeed, cognition and attention can be used to enhance the emotional aspect of aesthetic experience, as described in section 2.5.1. The human mind may create objects such as sculpture and painting in ways that depend to different extents on the explicit reasoning system and the more implicit emotional system. I know at least one sculptor who intentionally reduces cognitive processing by turning off attention to cognitive processing when creating works of art, and then follows this with an explicit, conscious, reasoning stage in which selections and further changes may be made, with the whole creation involving very many such cycles. Because cognition can by top-down cortical back projections influence representations at lower levels, it is possible that training, including cognitive guidance, can help to make more separate the representations of stimuli and their reward value at early levels of cortical processing. Rolls and Treves 1998, Rolls and Deco 2002, Rolls 2008. This top-down effect may add to the bottom-up effects of self-organization in competitive networks that also through repeated training help representations of stimuli to be separated from and made more different to each other. Rolls and Treves 1998, Rolls Neurobiological Foundations of Art and Aesthetics 469 and Deco 2002, Rolls 2008. These effects may be important in many aesthetic judgments that are affected by training, including the appreciation of fine art, architecture, and wine. 3.5.12 Wealth, power, resources, and reputation is already described. Wealth, power, resources, and status are attractive qualities, aesthetically attractive, because resources are likely to be beneficial to the survival of genes. Reputation is similar, in that guarding one's reputation can be important in reproductive success, trust is important in a mate, or in reciprocal altruism, and hormones such as oxytocin may contribute to trust. Lee et al. 2009. This provides some insight into the history of Western art, in which individual and family portraits frequently have as one of their aims the display of wealth, power, and resources. The clothes and background depicted in these paintings often show how wealthy and powerful their owners are. Commissioned portraits thus frequently emphasize beauty, status, wealth, and resources. Interestingly, because self-portraits are rarely commissioned, they are less likely to emphasize these characteristics. Coming 2009, they can reflect subjective knowledge of the person portrayed. An additional property that can add aesthetic value to a portrait is that an image of someone held dear is associated with the owner, and the attraction of photographic images is an example of this. Religion and states of spiritual ecstasy often aimed at achieving everlasting happiness should also be recognized as drivers of art. 3.5.13 The beauty of scenery in places. Many topological features of landscapes may be aesthetically attractive because they tap into brain systems that evolved to provide signals of safety, food, etc. Open space may be attractive because potential predators can be seen. Cover may be attractive as a place to hide. Appleton 1975. A verdant landscape may be attractive because it indicates abundant food. Flowers may be attractive as predictors of fruit later in the season. The color blue is preferred by monkeys, and this may be because blue sky, seen from the canopy, is an indicator of a safe place away from predators on the ground. Humphrey 1971. A clear red/orange sunset may be attractive as a predictor of good weather, and of safety overnight without bad weather. These factors do not operate alone to produce beauty, but may contribute to aesthetic beauty, which I argue is influenced by many of the factors described in this theory of the origin of aesthetics. 3.5.14 The beauty of music vocalization is used for emotional communication between humans, with an origin evident in other primates. Rolls et al. 2006. Examples include warning calls, warlike encouragement to action, and a soothing lullaby or song to an infant. It is suggested that this emotional communication channel is tapped into by music, and indeed consonant versus dissonant sounds differentially activate the orbitofrontal cortex. Blood et al. 1999, Blood and Zeta 2001, Involved in Emotion, Rolls 2014. Of course, the reasoning system then provides its own input to the development, pleasure, and aesthetic value of music in ways described in sections 3.5.10 and 3.5.11. 470 Edmund T. Rolls. What underlies the greater pleasure and aesthetic value that many people accord to consonant as opposed to dissonant music? I suggest that consonance is generally pleasant because it is associated with natural sounds, including vocal ones, with a single source that is naturally harmonic. A good example is a calm female voice. Dissonance may often occur when there are multiple unrelated sources, such as those that might be produced by a catastrophe such as an earthquake, or boulders grinding against each other, or strings on a violin that are not tuned to the harmonics of each other. Further, a human voice when angry, shouting, etc., and therefore by evolutionary adaptation effectively unpleasant, might have nonlinearities in, for example, vocal cords due to overexertion, and these may be harmonically much less pure than when the voice is calm and softer. 3.5.15 Beauty, pleasure, and pain. If a mildly unpleasant stimulus is added to a pleasant stimulus, sometimes the overall pleasantness of the stimulus, its attractive value, and perhaps its beauty, can be enhanced. A striking example is the sweet, floral scent of jasmine, which as it occurs naturally in jasmine and grandiflorum contains typically 2-3% of indole, a pure chemical which on its own at the same concentration is usually rated as unpleasant. The mixture can, at least in some people, and this may depend on their olfactory sensitivity to the different components, increase the pleasantness of the jasmine compared to the same odor without the indole. Why might this occur? One investigation has shown that parts of the brain such as the medial orbitofrontal cortex that represent the pleasantness of odors, Anderson et al. 2003, Rolls et al. 2003, Gravenhorst and Rolls 2009, can respond even more strongly to jasmine when it contains the unpleasant component indole, compared to when it only contains individually pleasant components, Gravenhorst et al. 2007. Thus one brain mechanism that may underlie the enhancement effect is a principle that brain areas that represent the pleasantness of stimuli can do so in a way that is at least partly independent of unpleasant components, thereby emphasizing the pleasant component of a hedonically complex mixture. A second factor that may contribute to the enhanced pleasantness of the mixture of jasmine and indole is that the indole may produce a contrast effect in the brain areas that represent the pleasant components of the mixture. An indication of this was found in increased activations in the medial orbitofrontal cortex, which represents the pleasantness of many stimuli, when the jasmine indole mixture was being applied, compared to just the jasmine alone, Gravenhorst et al. 2007. To the extent that the representation of pleasantness may drive hedonic experience separately from unpleasantness representations, Gravenhorst et al. 2007, and this might be facilitated by paying attention selectively to the pleasantness of a stimulus versus its unpleasantness, Rolls et al. 2008, then a factor might be the increased activation of pleasantness representations if there is a component to the stimulus that is unpleasant, and can enhance the pleasantness representation by contrast effect. Another example of enhancement of pleasant by unpleasant stimuli occurs when an odor becomes more pleasant if it is preceded by an unpleasant. Compared to neurobiological foundations of art in aesthetics 471 pleasant, odor, an effect represented in the human orbitofrontal cortex, Grabenhorst and Rolls 2009. A third factor is that the interaction between the pleasant, jasmine, and unpleasant, indole, components makes the complex hedonic mixture, jasmine and indole, capture attention, which in turn may enhance and prolong the activation of the brain by the complex hedonic mixture, and evidence for the capture of attentional mechanisms in the brain by the pleasant-unpleasant mixture has been found. Grabenhorst et al. 2011. These principles may of course operate in most areas where pleasant and unpleasant stimuli combine. Examples might include the pleasure we get from demanding terrain, high cliffs, high mountains, high seas, from spicy food that activates capsaicin, hot somatosensory, as well as gustatory and olfactory receptors, Rolls 2007, from tragedy in literature, although empathy makes a large contribution here, and from difficult feats, such as those performed by Odysseus, Rolls and Deco 2010. Let us consider the paradox of tragedy. For Aristotle, tragedy purged one of anxieties, Harewood 2008. Somehow the depiction of tragedy in drama, which raises unpleasant emotions such as sadness at the tragedy, can also as drama afford pleasure. Hume's explanation was that the beauty of the language and the eloquence of the artist's depictive talents are the source of pleasure. Hume 1757, Yale 1991. Is there more to say about this? Schadenfreude, gloating, pleasure at the distress of an envied person, is associated with activation of brain areas that respond to pleasant stimuli. Shamansoi et al. 2007, Takahashi et al. 2009, and I suggest is related to the evolutionary origin of competition between individuals, and winning the competition. It is probably not an important factor in the appreciation of tragedy and drama. What may be more important is first that we, and this is especially strong in women, always want to know what is happening to whom, and gossip has evolutionary value. Dunbar 1996, in that this can provide information about how others are likely to treat one, and more generally, about the things that can happen to people in life, and from which lessons can potentially be derived. Second, the ability to empathize with another's emotions, and indeed to be good at empathy and find it rewarding, may also be important in communities in order to facilitate kin or reciprocal altruism. Ridley 1996. Third, the ability to consider a theory of other people's minds is adaptive in facilitating prediction of their behavior. Frith and Singer 2008, and fascination with this subject should again in an evolutionary context be rewarding and be associated with pleasure. It is suggested that these three factors are at least important contributors to the pleasure that people find in tragedy and drama. The same factors, I suggest, are also important contributors to the popularity of novels. In the cases of both drama and novels, we know that they are fiction, or at least that the events described are not happening to the spectator or reader, and this helps to make them particularly rewarding ways to learn about social relations in life events because there is no risk to the spectator or reader. Knowing that the work of art, music, literature, painting, sculpture, is a fiction may also account for why the aesthetic emotions are not as long-lasting, and are not as motivating, as the goals in real life. 472 Edmund T. Rolls 23.5.16 Absolute value in aesthetics and art. The approach described here proposes that what we find aesthetic has its roots and origins in two main processes: gene-specified goals, rewards, and punishers, and the value that is felt when our reasoning system produces and understands elegant and simple solutions to problems. Rolls 2012. What implications does this have for absolute aesthetic value? The implication is that while there is no absolute aesthetic value that is independent of these processes, we will nevertheless find considerable agreement between individuals, especially when the aesthetic value being judged has its roots in the two main processes described. However, as illustrated here, there will be variation for good evolutionary reasons between what different individuals find of value, and there will be variation in individuals' thought processes caused by their cultural heritage, and by noise in the brain, which is an important component to creativity. Rolls and Deco 2010, Rolls 2012. For these reasons, and because aesthetic value is multifactorial, i.e. is influenced by multiple conscious and unconscious processes, we must expect variation in aesthetic value across people, time, and place, with no absolute aesthetic value. 23.6 is what is attractive also beautiful in aesthetic. I wish to counter a possible objection to the theory of the origin of aesthetics described here. This is that some of the goals specified by our genes, such as the reward value and pleasantness of a high-energy, high-fat diet, might seem rather unsavory, and not quite aesthetic. The point I make is that it is not just the gene-specified rewards and punishers that cause stimuli to have aesthetic value. My proposal is that the reasoning, rational, system also contributes to aesthetic value in a number of ways. It makes rather longer-term goals attractive. It introduces a further goal that innovation is attractive, as this is likely to help solve difficult problems and move the person into a new part of state space where the person may have an advantage. It introduces the use of syntactic relational structure to provide another way of computation. Problem solving using this reasoning system is encouraged by simple, elegant solutions which are rewarding and which have aesthetic value, as described above. These factors would help the sophisticated structure in the Bach partita and fugue to contribute to what we judge as aesthetically pleasing, because such music taps not only into our emotional systems but also into the systems that provide intellectual pleasure because difficult and complex structural problems are posed, and solutions to these difficult structural problems are provided which provide aesthetic pleasure. In this sense, aesthetic value may have its roots partly in gene-specified rewards and punishers, but also in the pleasure that the rational system can provide when it is posed, and finds, elegant and simple solutions, which by parsimony are likely to be correct, to complex problems. For this reason, emotions may not be perfectly aligned with aesthetic value. Although both have their origin in gene-specified rewards, emotions may be produced by any one of a large number of reinforcers, whereas aesthetic value usually includes contributions of the reasoning, rational, system, as just described. Neurobiological foundations of art in aesthetics 473 Art as a whole is a larger issue than aesthetics and beauty. The content of art might, I suggest, be seen as the result of multiple separate trajectories through a state space in which each trajectory is guided by the origins of aesthetics, products of adaptations for survival and of sexual selection for useless sometimes handicapping ornament, and rational thought to develop structure in which an elegant and simple solution is pleasing, and depends on each previous trajectory, the history of art in each culture. Each trajectory is not itself deterministic because it is influenced by noise. Rolls and Deco 2010, Rolls 2012, as is Darwinian evolution. Thus, future trajectories cannot be predicted. In each trajectory, though, a number of factors dominate, including newness, which is biologically attractive as argued earlier, the quality of wildness, as in Beethoven's late string quartets, as well as what we rationally find aesthetic, as described earlier, and what survival and sexual selection have also provided in us as some of the origins of aesthetics. 23.7 Comparison with other theories of aesthetics. Much research I have performed shows that there is a perceptual representation of objects formed in cortical areas that is kept separate from the representation of the effective value of objects, which happens further on in processing, in brain regions such as the orbitofrontal cortex, and in an area to which it projects, the anterior cingulate cortex, and the amygdala. See figure 23.2, Rolls 2008, 2014. There are good functional and adaptive reasons for separate representations of objects and of their effective value. We can still see and recognize objects, including tastes, smell, the sight of objects, etc., even when they are not rewarding to us. For example, if they are foods and we are not hungry. We are not blind to objects when they are not rewarding or punishing. Moreover, it is adaptive to be able to learn about where we have seen objects, people, etc., even if they are not currently rewarding, so that we can find them later when they are needed. Thus there is strong neuroscientific evidence, and sound biological arguments, for separate representations of perceptual objects and of their effective value. Baumgarten, 1750, expressed this thought in his Aesthetica when he suggested that sensation, the use of the five senses, is separate from sensibility, which is something more, a kind of intuition/cognition/formulation of the thing which judges it beautiful, and in doing so gave rise to the term aesthetics. Harewood 2008. Before this, abstract questions such as what is beauty, what is art, had not been discussed generically in philosophy, although Aristotle had discussed the social role of drama as purging us of ever-present anxiety, and Plato had dismissed poetry as obfuscating by sending the mind reeling into hypnotic trances instead of focusing on rational deductions and argument. Harewitz 2008. David Hume, 1777, takes a broad view of taste, which engages beauty, and argues for 5 standards of delicacy of taste that might be shown by experts. Strong sense, united to delicate sentiment, improved by practice, perfected by comparison, and cleared of all prejudice, can alone entitle critics to this valuable character, and the joint verdict of such, wherever they are to be found, is the true standard of taste and beauty. Hume's difficulty is that he believes taste is objective, because delicacy is the proving instrument for truth, but 474 Edmund T. Rolls instead, taste is a circular and constructivist enterprise. Harewitz 2008. My approach has in contrast a clear foundation for aesthetics and brain function in its evolutionary design, with clear views about how it includes rational thought which provides its own pleasures, and about how art can idealize beyond the normal world by building on these foundations and origins. Immanuel Kant, 1724-1804, distinguishes between liking something and finding it beautiful. According to Kant, when I find a painting beautiful, this is not conditioned by any causal relation between its properties and my pleasures. For Kant, the judgment of beauty carries the weight of that others should judge it beautiful too, so his theory has moral implications. His judgment of beauty is a disinterested judgment, one that is not peculiar to him. He wants the beauty to be in the person, but not causally dependent on the properties of the object in the world such as the pleasure it produces. Kant 1790. He thus appears to be committed to an objective and universal view of art, with exactly how this view is arrived at not at all clear. The biological and neuroscientific view that I propose indicates that, in contrast, art is not universal or objective, but instead can be judged to be good art if it taps into many of the human rational and gene-based reward systems. See further section 23.6, with therefore individual difference is expected, as described in section 23.5.16. Darwin, 1871, recognized that evolution can occur by sexual selection, when what is being selected for has no inherent adaptive or survival value, but is attractive to potential mates, intersexual selection, or helps in competing with others of the same sex, intrasexual selection. His view was that natural beauty arose through competition to attract a sexual partner. His process of sexual selection through mate choice, the struggle to reproduce, not to survive, drove the evolution of visual ornamentation and artistry, from flowers through bird plumage to human self-adornment. Many have developed or ascribed to this idea, including Thorstein Veblen, 1899, Ernst Gombrich, 1977, Amos Zahavi, 1978, and Dennis Dutton, 2009, and Miller, 2001, has proposed a sexual selection theory of art. The implication of Miller's theory is that art has to do with what are frequently useless ornaments, useless in the sense that sexual selection is for characteristics that do not have survival value, but are usually just attractive because they are handicaps and are indicators of fitness. I agree that useless, handicapping ornamentation produced by sexual selection does play a role in aesthetics. However, the sexual selection theory does not therefore have much to say about the utilitarian arts such as simple design and architecture. Perhaps the structure of a piece of music can appeal, and be pleasing, because it taps into our syntactic system that finds that adaptive, survival value-related, elegant, and simple solutions to problem-solving produce pleasure. As I argued above, interest in social relations and knowledge about them is adaptive and this has survival value as it may help to understand who is doing what to whom, and more generally to understand what can happen to people, and much fictional literature addresses these issues, and is not purely ornamental and without inherent value. Thus, although Miller may well be right that there are aspects of art that may be primarily ornamental and useless, though attractive to members of the opposite sex in courtship, I suggest that a great deal of art has its roots in neurobiological foundations of art and aesthetics 475 goals that have been specified as pleasurable or unpleasurable because of their survival or adaptive value, whether as primary reinforcers, other stimuli associated by learning with these, or rewards of a more cognitive origin that accrue when difficult cognitive, syntactic, problems are solved. I also emphasize that some of the characteristics emphasized by sexual selection may have some inherent survival value. Sections 23.5.3.1 and 23.5.3.2. My theory, the roles theory, of the foundations of aesthetics and art thus specifies the roles of Darwinian survival or adaptive selection and sexual selection in aesthetics, Rolls 2011A 2012. It is thus thoroughly Darwinian. A key idea is that many of the things that provide pleasure, or its opposite, do so because they are, or are related to, the gene-specified goals for action. Motivational states arise when trying to obtain these goals, and emotional or affective states when these goals are obtained, or are not obtained. These states are associated with affect and value, and with subjective pleasantness or unpleasantness, because it is an efficient way in which genes can influence their own reproductive success, fitness, and much more efficient and effective as a Darwinian process than prescribing that the animal should make particular responses to particular stimuli. Rolls 2014. The theory is that aesthetic value has its roots partly in these gene-specified rewards that have survival or adaptive value, but also in the pleasure that the rational system can provide when it is posed, and finds, elegant and simple solutions, which by parsimony are likely to be correct and hence adaptive, to complex problems, and to some extent in sexual selection. What makes good art can be influenced by many factors, as described here, so it is complex and multifaceted, and these factors must include whether the effect of the art is for good or for ill. It also follows that attempts in aesthetics to produce a systematic account based on consistent explicit beliefs will not succeed because many factors that are not necessarily consistent with each other are involved in aesthetic values, and because some of these factors operate at least partly unconsciously and non-propositionally/non-syntactically, that is, using computational systems in the brain that do not involve reasoning. 24.1 Introduction. Every compound stimulus that impinges upon the organism can be perceived in multiple ways. For example, a visual scene will be unlikely to have an invariant impact on a population of viewers, as each will perceive, sense, associate, respond to the display in a different way, depending on the history of experience, on momentary state variables, and probably genetic determinants. Even the repetitive presentation of the same display to one observer will be likely to have different effects, each presentation being influenced by the effects of prior presentations, as we will discuss below. Perceptual systems, attention mechanisms, and cognitive processes habituate or adapt to repeated input and, thus, change their response to the input. An important set of determinants of variation to visual, or auditory, tactile, olfactory, taste, input between viewers and within viewers themselves is the notion of multiple attributes of complex stimuli. For example, any photograph or painting can at any given time be viewed on the basis of many different parameters depending on the momentary state, e.g. mood, expectation, and history, education, cultural background, experience, of the viewer. This holds for the viewing of any complex stimulus, including any work of art. A work of art can be considered as a compound of attributes or qualities on the basis of which it will be perceived as well as evaluated. These attributes can be relatively simple variables such as color, size, and grain. They can be emotionally charged variables designated by terms such as novelty, beauty, spiritual, sublime, monumental, or formal aspects of a work that can be defined by basic compositional terms such as form, space, balance, and harmony. They can also be information with associated value based on representational and figurative content loaded with meaning, as in expressionistic and representational art. Then there are complex qualities related to experimentation, playfulness, innovation, and conceptual art. See section 24.4 below. The number of possible attributes of a compound stimulus is endless and a list of the attributes of a particular work can be many or few, depending on the viewer's state and experience. A sophisticated viewer will be able to perceive as well as verbalize more attributes than a novice. The viewer's evaluation of a work of art is related to the experienced attributes of the work. Here we can already ask whether or not these functional attributes must be 480 Alexander J. Houston and Joseph P. Houston consciously perceived to affect the evaluative process. Since we have no notion of an answer to this, we will simply assume that any experience of an object, be it conscious, with the viewer being aware of it, or unconscious, has a corresponding representation in the brain which can lead to an action, i.e. a response to the experience, and thereby influence the evaluative process. We proceed on the basis of the postulate that the multiple attributes of a work determine the viewer's evaluative response to the presentation. It follows that if one can define the functional attributes of a work and their relative importance and integrity, we should be able to predict how the work is evaluated and potentially have a measure of its worth for the particular viewer. Accordingly, we will here present an attempt to formalize the relationship between the multiple attributes of an image in determining the viewer's overall evaluation of the work. Our approach to modeling the aesthetic judgment can be seen in the context of earlier attempts at computational aesthetics as, for example, expressed by the mathematician G. D. Birkhoff's formula or aesthetic measure, which was based on the assumption that aesthetic objects derive their quality from their numerical or geometrical characteristics, that is, that the pleasure derived from an image equals the ratio between the order, 0, and the complexity, C, in the object, M equals O/C, Birkhoff 1933. Most of the many attempts at formalizing aesthetic experience dealt with the analysis of individual attributes of a work or subsets of such, as for example the debate on the role of the golden ratio, phi, as a source of architectural aesthetics, whereby two quantities are said to be in the golden ratio if the ratio of the sum of the quantities to the larger quantity is equal to the ratio of the larger quantity to the smaller one, plus equals AB with the following solution, equals plus equals 152. 1.61803398887 Baumgarten, 1739, already declared the laws of beauty, like those of nature, to be amenable to systematic, empirical investigations via a new science, which he named aesthetic, the judgment or estimation of taste or of the beautiful, the object of which was to assess perception whereby particular representations are combined into a whole, that is, to translate the unity of perception into measurable variables. Subsequent formal mathematical approaches, Lapin et al. 1995, Winger and Townsend 2001, can be said to derive from the Gestalt psychologist's attempts to account for particular aspects of our perception of motion, faces, texture, etc., on the basis of our ability to generate and recognize whole forms from simple elements, with the emphasis on the whole being greater than the sum of the parts. Unlike the many attempts to model particular attributes of a work and their role in aesthetics, we will present a formal theory of their individual and compound roles in the resultant total evaluation, appreciation, of a display or work. We believe that such a formal approach to dissecting the elements of displays and objects can serve as a conceptual guide to our active viewing and understanding of the complexities of evaluation of works of art. Aesthetic evaluation of art 481.24.2 Qualia, QS, and aesthetic evaluation from here on we will arbitrarily focus on visual presentations and designate their attributes as qualia. The term qualia, singular quali, is a loose designation for a concept that encompasses how we experience the world, e.g. Lewis 1929, Chalmers 1995, Horton 1984. Synonyms for qualia might include features, attributes, percepts, qualities, sensation of, or subjective experience of an image. There is no consensus in the use of this term, which has engaged many philosophers in their attempts to account for issues of phenomenology related to perception, subjective experience, and the mind-brain relationship. We use the term qualia to refer to a strictly subjective experience of the observer in response to a stimulus. A qualia is a virtual property solely an inner experience that has no physical reality in the sense of being a property of the stimulus, display, or object itself in the physical world that is being viewed, e.g. Schrödinger 2001, Perkins 1983. The major variables we postulate as determinants of the subjective evaluation, E, of an image or any work of art are its attributes or qualia, Q. Each qualia has a value, G, which is a measure of its integrity or goodness, as well as a value weight, W, which is its relative importance for the particular work. The weight and importance of the qualia determine its level of dominance or primacy over other qualia and also the nature of the interactions between the constituent qualia and their influence on the momentary subjective experience of the work. How do these variables relate to each other in deciding the subjective evaluation, E, of the work or image? We can arbitrarily posit the following relationship, equation 1, which states that the subjective evaluation of an image, E equals subjective overall quality, is a function of the number, N, of inherent qualia, Q, that are considered to compose the work, whereby each qualia has a value, G, which is a measure of its integrity or goodness and a value weight, W, which determines its relative importance for the work. Values for W and G can be conceptualized to be on a scale, e.g. from 110, 100, C. Below. Equals EGIWGIN1, 24.1. We have arbitrarily presented a simple additive effect of the multiple qualia on the overall evaluation. Such an additive relationship could hold, for example, for the purpose of comparing different works with each containing the same number of qualia, such as multiple works by the same producer. Different goodness values, G, and weights, W, for identical qualia would then decide different degrees of the overall evaluation of the compared works. However, a simple additive relationship cannot hold for comparisons between works with different overall numbers of qualia, since it would imply that the greater the number of qualia experienced, the higher the overall evaluation would be. We must consider this to be unlikely as a general law, since it would imply that simply adding qualia to a work would improve/increase the E of a work, which cannot be true. Therefore, we must assume some kind of limit to the maximum level possible for E. Consequently, for purposes of comparing images or works with divergent numbers of qualia, 482 Alexander J. Houston and Joseph P. Houston, we postulate a limit to the maximal possible E for any particular work. For this purpose, as a first approximation, we posit that not the sum, but the average or mean of the number of qualia and their properties determines the overall E, by dividing sum by the total number of qualia, N, as in equation 24.2, equals EGWQNIIN1 equals ENGWQ1IIN1, 24.2. We have also arbitrarily stated a multiplicative relationship between W and G of a qualia, whereby the value of each in goodness, G, is multiplied by the value of its weight or importance, W. Another perhaps more reasonable relationship could be, for example, an additive one, whereby the rating of goodness, G, of a qualia is added to the value of its weight, W, as in equation 24.3, equals ENGQWQ1, IIIN1, 24.3. We could hypothesize other more complex relationships between the individual Q and their influence on E. For example, one could argue that the whole is more than the sum or mean of its separate parts, a reasonable assumption which will have to wait for an adequate formula. However, as we discussed below, the qualia that are high in goodness and importance interact, harmonize, and compete to create the whole E. See section 24.9. Thus, the result of the interaction between qualia in terms of synchrony, harmony, etc., can become by itself an important qualia. In the meantime, in order to illustrate the usefulness of this type of model, we will continue to employ the multiplicative relationship between W and G as expressed in equation 24.2 as the basis for our argumentation. Models as we have presented them can be useful for conceptualizing relationships between variables. However, a model will have significant utility only if it can be tested and disproven and eventually be adapted to empirical reality. As we will argue later, this model may have such heuristic value in making empirically testable predictions regarding the evaluation and composition of works of art. In an experimental test of the relationship between qualia and deciding E, posited above, one could query a viewer as to, for example, which qualia are inherent in the work, and to rank individual discernible QS in terms of their importance, W, and goodness, G, via a rating scale of, say, between 0 to 10. Works of art such as a painting or photographic image can surely be analyzed or discussed in terms of the weight and goodness of perceived QS. One can thus systematically fragment and decompose the image or work, dismantle it by identification of its functional, perceived, qualia. Such a systematic dissection of a work could also be performed in the service of testing the validity of the relationships postulated here. For example, it would be possible to test the utility or validity of the formulae empirically by comparing the evaluation of raters on a scale based simply on their intuitive appeal and one based on explicitly defined parameters. Aesthetic evaluation of art 483 of qualia inherent in the formulae. The degree of concordance between these evaluations could be a basis for hypotheses as to how to improve the formulae to improve the approximation of reality in aesthetic judgment. 24.3 Violation and extraction of qualia. We can now ask how the evaluation E of an image would be influenced by the elimination of or damage to a particular qualia Q. From the formulae above, it follows that the smaller the number of QS that comprise an image, the more dependent is the overall appraisal, E, of the work on the integrity, G, and weight, W, of its individual components. Conversely, as the number of QS in the work increases, the less impact will W and G of any individual qualia have on the overall subjective evaluation. This prediction is independent of whether we take the overall number of QS or the mean number of qualia to constitute E, and independent of whether the relationship between W and G is additive or multiplicative. The relationship between the relative weight of an individual Q to the total number of QS in the work, we hypothesize that the number of QS in the work will also determine the relative weight of each in deciding the overall E. Thus, we should adapt the equation to account for this relationship, which is likely to be an inverse correlation between number of QS and their individual weights. We can now ask as to the influence on E of eliminating or damaging a particular qualia. We postulate that the subjective evaluation E of an image that has been modified by the extraction of a qualia Q, X, with X equals 0, N, will be a function of the number, integrity, and weight of the remaining Q relative to the original total number of defined QS and their integrity and weight. This relationship can be expressed as follows in equation 24.4, E n x GWQ n GWQ GWQ n x n GWQ n GWQ n x GWQ 11, I n x I n I n x I n I n x I n 1 equals times equals 24.4. It follows from this relationship that the more qualia that are inherent in the work, the more resistant will be the value of E to an extraction or violation of any particular Q, since more QS are left over to carry the image, i.e. its level of evaluation E. Conversely, the smaller the number of QS in the image, the more vulnerable will be the residual overall evaluation of the work E to elimination or violation of any individual qualia. The same holds for the violation of a particular Q in the work due to a low level or failure of goodness G or impact W, that is, the fewer the definable QS in the work, the more impact will any particular Q have on E. Therefore, a low value of G and / or W of any Q will have a more critical influence on E than in a work that is characterized by a higher number of qualia. We can perform virtual as well as real experiments to test the predicted relationship between number of QS and the impact of modifying or eliminating a particular qualia on the evaluation of the work. For example, we could change the characteristics of an 484 Alexander J. Houston and Joseph P. Houston obvious source of qualia in works composed of relatively large numbers of associative QS, Hieronymus Bosch, and compare the relative effects on the evaluation E with the influence of the violation of AQ, e.g. color, in minimal artworks, e.g. by Barnett Newman or Ed Reinhardt, that contain fewer obvious discernible QS. Equation 24.4 predicts that the evaluation of a minimalist work will be influenced more by such a violation or extraction of AQ. The greater impact of a violation of AQ in art which is characterized by the use of few but powerful QS would actually imply a higher degree of difficulty in creating such work in comparison to work embellished with more QS. In fact, Greenberg has espoused the deliberate refusal of particular qualia and the systematic delimitation of such in the development of modernism. Greenberg 1961. His analysis of the gradual development of modernist art can be seen in terms of the dispensing with of traditional qualia, such as three-dimensionality. Painting, he states, has made itself abstract and achieved autonomy by divesting itself of everything it might share with sculpture. Painting should be self-critical and address only its inherent properties or QS, namely, flatness and color. Looking at the content of art from the standpoint of its QS can contribute to an understanding of the work independent of the language used in descriptive analysis. For example, minimal art has been defined as being the maximal expression of formalism by its elimination of emotional elements, QS, characteristic of informal art and abstract expressionism. Such works can be characterized as 1. Containing few discernible QS beyond the simple formal ones, e.g. proportion, 2. Devoid of QS with common associated properties and the accompanying emotional effects, and yet, 3. Containing abstract QS that may be difficult to label, other than with descriptors such as purity, spirituality, peacefulness, simplicity, elegance, etc., which may have emotional components, but not of the kind associated with everyday meaningful and identifiable concepts, ideas, objects, or events. The achievement of this category of QS may define the teleology of minimalism. A similar analysis applied to other art forms will most likely arrive at different categories of dominant QS that define it as a style or direction of art. 24.4 Taxonomy of qualia. Such an individual analysis of an artwork can encompass 1. Simple basic qualia, such as color, size, brightness, texture, and grain, brushstroke, transitions technique. 2. Emotionally loaded QS related to novelty, conflict, beauty, and the standard emotions such as love, hate, disgust, fear, desire, and laughter. 3. The formal compositional QS, such as form, space, perspective, balance, harmony, or disharmony, that are taught as fundamental tools of the craft. 4. QS with associated value of items or ideas, based on representational and figurative content. 5. QS derived from the flow, interaction, and balance between concurrent QS, see section 24.9, and 6. The higher order, poetic, aesthetic, philosophical, ideological, and spiritual QS. It should be possible to establish a classification scheme of the types of QS to be found in images or works of art and on that basis describe artworks objectively, independent of epochs, schools of art, and content descriptors. Aesthetic evaluation of art 485 24.5 Viewing art on the basis of qualia. We will from here on use the term qualia rather loosely to refer to particular attributes or qualities of a work of art or architecture. The notion of qualia can also guide us in understanding the development of a work of art. To illustrate such an approach, we can take an actual example of a work of art and trace its development in stages to finality, as the artist defines it. The first two images in figure 24.1 present actual steps in the course of the production of a work of photographic art. There were many other steps in between these. In the top left, the picture is still structured in layers, the plastic ground, the red surface, blue surface, and back wall. In step 2, top right, the focus is on the red plus blue surface and the scaffold in between, giving the structure more monumentality. In the final version below, the structure is lower and appears heavier, whereas the space is clearer and takes on a function in the picture, and the numbers become important in filling the space and defining the background. We can see the progressive flattening of the image approaching that figure 24.1 steps on the way to a final photograph by Hans Norberg, 2012, 175 x 140 centimeters. Bottom image is the final. Copyright BG Bildkunst, Hans Norberg, 2012. 486 Alexander J. Houston and Joseph P. Houston of a painting. Whereas the steel scaffold and the colors remain invariant, major changes lie in the surface of the base perhaps to approximate an impression of water, the adjustment in hue of the colors and the proportions of the elements to each other in the frame. We can, on the basis of this progression, infer some of the invariant QS and the artist's priori intentions. 24.6 Eliminating AQ. We can also perform post hoc experiments and violate qualia in works of art and assess the influence on our evaluation. For example, in figure 24.2 we extracted the postcard from the center of the photograph. We can see that its removal has a profound effect on the image in terms of balance, proportion, depth, and color fundamental QS in artworks. However, the extraction also influences other more subtle QS in this work. The postcard takes up various central themes in the picture. For example, art historical QS. The postcard is of a painting by Jan Vermeer and is dominantly positioned in an arrangement where there are various references to art, music, and literature. Aging as AQ. The postcard is yellowed and creased and the other objects are similarly dusty and used. The hat the lady wears a red, fluffy, elegant hat at an angle. The baseball cap is blue, hard-rimmed, and common and at an angle on the books. Overall poetic elements, QS, are influenced by the extraction of the postcard. We have also violated important QS in two architectural masterpieces in figures 24.3 and 24.4. We can now ask whether and how the violation or elimination of one Q will influence the poignancy and weight of the remaining QS in the overall evaluation. The equation 24.4, as a first approximation, is based on the simplified assumption that after a deletion of any individual Q, the values G and W of the remaining QS stay the same. An alternate and more valid assumption might be that after elimination or subtraction of a qualia, X, the G, and W values of the remaining QS will change, with the consequence that the overall E might even increase, instead of always decreasing as in equation 24.4. Such a relationship can be expressed in the manner shown in equation 24.5. Here y equals nx, the number of remaining qualia q, y0 equals the original state, x equals 0. And the number of extractions, gi and wi are a function of y. EY GY WYQ GY WYQ GY WYQ GY WYQ and XI and XN I and NI and XN XI and 1111 1 I 00 I equals 24.5 24.7 rapport between producer and viewer. Interestingly, we can employ our basic model to also account for the failure or success of a work of art. For example, a lower evaluation E given by the viewer than that expected by the producer can be a result of a discrepancy between the qualia that are intended / perceived by the artist and perceived by the viewer. Accordingly, the bigger the discrepancy between the evaluations of artist and viewer, the less likely it is that the work will be understood. We can measure the degree of dissonance between viewer and producer by aesthetic evaluation of our 487 figure 24.2 extraction of part of a photograph by Christopher Moore, Studio, 2012, 69 x 95 centimeters, top, original, bottom, defaced. Copyright Christopher Moore. 488 Alexander J. Houston and Joseph P. Houston taking equation 24.4 and making a ratio between the evaluations of the producer, P, and viewer, VJE equals PE/V, 24.6. This relationship is shown in equation 24.6, whereby the ratio between the evaluations, ES, of the producer, EP, and viewer, EV, provide a metric of the discrepancy, D, between these, namely day. The degree of proximity to value 1 provides the measure of rapport between producer and viewer. A divergence between the E values of producer and observer can be a result of different W and / or G of the same Q, or to different QS recognized by producer and observer. Of course, this measure of dissonance or concordance is applicable to comparisons between any other populations, such as between expert and naive viewers. 24.8 Invariance of qualia. As we have already stated, we assume that when we view a work we consciously or subconsciously assess it on the basis of qualia and their interactions. With experience we may become familiar with the criteria for goodness, quality, and importance of the qualia as dictated by the experts, e.g. the market, critics, artists. Which QS are discerned in a work and how they are weighted and evaluated are, of course, influenced by cultural, political, historical, theoretical, and contextual variables. Hulot and River, 2013, have admirably compiled and categorized the environmental, social, and historical factors that determine the viewer's detection and evaluation of qualia and their properties in works of art. In spite of the great number of possible sources of variation and the presumed subjectivity involved in the response to complex displays, there can be a remarkable degree of concordance and agreement in the evaluation of art objects and in the extraction of qualia and their relative impact. Such consensus is undoubtedly the result of acquired notions, common history, and cultural influences, marketing pressures, and suggestion. However, there is also evidence for genetic variables that dispose the viewer to recognize, value, or avoid attributes of images. How we perceive and evaluate objects in the world is partly determined and limited by built-in physiological mechanisms that have developed in accordance with evolutionary and ecological pressures with survival functions. These can be built predispositions in the perception of and responses to relatively simple qualia such as proportions, balance between elements, color combination, novelty, etc., but also to more complex information such as object and action categories, e.g. Brown et al. 2011, Huff et al. 2013, Ishizu and Ziki 2011, Ziki 2000. Since, as we have stated above, E can be influenced by innumerable variables, including context, history of exposure, and current state variables of the viewer, e.g. time of day, transient mood, concentration level, health, we can ask to what degree a measure of E can be reliable, that is, what is the variability in the measure of E with repeated viewing of the same display by the same observer. We can also ask about the concordance of E within a particular population of viewers, to what extent does a subpopulation concur in the inherent qualia and eventually of a work and how consistent is such a population E. We could hypothetically as well as empirically also compare the mean ES of different aesthetic evaluation of our 489 subpopulations of viewers, e.g. based on levels of education, demographics, etc. It should also be possible to detect invariance in the properties of works by the same artist, to identify QS that define or characterize the aura of a particular artist or class of artists. An example of how an individual artist's work can be discussed on the basis of idiosyncratic QS has been carried out elsewhere. Houston 2002A, 2002B. 24.9 The problem of concurrent qualia, poignancy, fading, and interplay of Q with the perception, registration, and judgment of a work are a function of the actions of its multiple qualia on the observer. We must ask whether and to what degree multiple parameters, attributes, or characteristics of a display can be simultaneously processed to result in E. We cannot rule out the possibility that the nervous system can simultaneously process different qualia in parallel. Even if we accept this possibility, we can ask whether a viewer can simultaneously also attend to multiple QS in an image or work, whether consciously or unconsciously. 24.10 Poignancy. To address the issue of the processing and impact of multiple concurrent QS on the observer, we can make the following assumptions or hypotheses. 1. Qualia with high values of weight, W, will predominate over QS with relatively low weight and poignancy. Accordingly, the probability of a qualia having an impact on the observer will correlate with its weight. 2. Similarly, qualia with high quality or goodness, G, will predominate over QS with low values of G and, as with weight, will have a hierarchical probabilistic advantage correlated with goodness. 3. As we have posited an interaction between W and G in determining the value of judgment E, it follows that this interaction, in our case stated arbitrarily as multiplicative, provides a compound measure with a relative probability in terms of relative dominance over other QS and the impact on the observer, which we can designate as poignancy, a Q in itself which will determine processes related to detection of an attention to the QS. As we have emphasized, the fewer the number of QS in a work or display, the more important each individual Q will be in deciding overall E, and most likely, the more poignant it is, the higher will be its weight, that is, the number of QS in a work will also determine the relative weight of each in deciding the overall E. Also, in reference to the earlier section on violation of Q in equation 24.5, we emphasize that violation or manipulation of one Q is likely to influence the weight and poignancy of the remaining ones, with a probable effect on total E. 24.11 Fading or decay of Q. We hypothesize that an attribute of any stimulation will not remain invariant over the duration of viewing. Thus, although the poignancy of a Q may increase as a function of enhanced recognition and attention to it, it is also likely to fade or decay with time of observation. Such fading of QS can be a consequence of habituation, satiation, fatigue, and boredom, or due to shift in attention to competing QS. Such processes are well known to 490 Alexander J. Houston and Joseph P. Houston influence perception and can occur at various levels of the nervous system, including the basic receptor level, such as the retina. The issue of fading qualia has also been treated by Chalmers, 1995. We posit that each Q has a specific rate of decay or fading. The rate of decay determines its dominance over competing QS over the time of viewing, as well as its interaction with QS that replace it. See section 24.12. The rate of decay of a Q is likely to be related to its combined weight and goodness. Furthermore, the rate of fading is also likely to be a function of the competing QS in the work, that is, the fewer the competing QS, the slower should be the rate of decay. Such fading of QS is related to processes of attention. The viewer's attention may shift to competing QS. It follows that the fewer competing QS there are, the less likely that attention will shift and the fewer QS to which can attention be shifted. Such fading allows a second level Q to assume a higher level of poignancy. As new dominant QS also fade out, there will be an emergence of new and previously faded QS. This process of substitution of QS enhances the novelty of QS and in itself provides an overall dynamic process, which may be considered to influence the overall impact of a work of art, or of any complex display, on the viewer. Thus, the subjective impact of a display is not a static all or none effect on the observer and on his or her nervous system, but a continuous process involving the flow of information of the QS that define or constitute the experience. 24.12 Interplay of QS. The concept or process of fading of qualia underlies an important form of interaction between QS. Qualia can interact in several ways. For example, 1. They may influence each other in powerful ways to create new compound QS. Their virtual simultaneity can have additive properties to define a whole. 2. They also serve as each other's context. 3. Due to the fading out we hypothesized above, we can postulate that interactions between QS are not merely parallel, but also sequential and dynamic. For example, in the case of an art object that is presented to the observer statically, painting, photography, an important process pertains to the interplay between QS during the process of evaluating the image. Such an interaction between competing dominant Q can be conceptualized as a dynamic reciprocal flow between them that can perhaps determine harmonic properties of the work. When we confront an image, our perception thereof is not invariant, but on the contrary, is determined by such a flow between the images QS, whereby one or a set of such can dominate and recede in rapid succession. For example, when viewing figure 24.1, the associated elements for QS, such as the impression of water or the steel scaffold, can predominate at one point in time, whereas compositional QS, color, proportion, may dominate at another moment. Such a switching between component QS can be willed, since we can consciously decide to focus on one or another, or it can be uncontrolled due to fading of QS, as one clearly displaces another in predominance. Uncontrolled switching between perceptual elements for QS is illustrated by the well-known reversible figures of Gestalt psychology. Of course, the effect or memory of one Q will hereby influence the interpretation or effect of the subsequent Q. There are deliberate goals in the visual arts to present the unitary whole in the work as one Q instead of as a composition of aesthetic evaluation of art 491 parts, particularly in so-called minimalist works, that attempt to reduce a concept to its simplest and purest form by a minimal use of geometric shapes, colors, lines, and progressions. 24.1 Qualia in architecture for art forms that are dependent on temporal or sequential properties of QS, such as music, architecture, and literature, or dependent on different perspectives for viewing, such as architecture and sculpture. The exact nature of the interaction between elements in their sequence and order can be critical. A work of architecture can potentially be seen from an infinite number of perspectives as it is four-dimensional, 3 dimensions in space plus time. One can enter the structure, traverse, touch, and use it. It cannot be viewed primarily from the standpoint of visual art. Architectural design can involve a string of logical and causally related sequential processes. Thus, the QS in architecture can display a mutual dependency in terms of purpose and idea. The preservation of ideas and conceptual intentions throughout the process of design and building stages to the finished product is a major complex Q. The degree of understanding of these cardinal design ideas will strongly influence the evaluation of the product. For example, the process of employing as little as possible to achieve as much as possible is a major Q of minimalism in architecture, with the notion that less can be more, as fewer QS gain more weight in the impact of the whole. From this perspective, architecture is more complex than, say, a painting, as it cannot be evaluated in toto from one point of view. Its QS include functional aspects, material and tectonic elements, aesthetic as well as contextual properties. Parts of a building have specific functions which can be viewed in isolation but also in relation with the other sections of a building, its environment, and history. Consequently, the possible basis for evaluation can be complex or simple, depending on the viewer's focus, on the primary point in QS. We will here examine some architectural QS with examples taken from different architectural traditions. 24.14 Antique to consider just one Q, namely proportion, as emphasized around 25 BC by Marcus Vitruvius Pollio in De Architectura. Proportion is a correspondence among the measures of the members of an entire work, and of the whole to a certain part selected as standard. From this result the principles of symmetry. Without symmetry and proportion there can be no principles in the design of any temple, that is, if there is no precise relation between its members as in the case of those of a well-shaped man. Vitruvius 1914, proportion in architecture refers to the ratio of the length, width, and height of a building, a facade, or component. The Parthenon in figure 24.3 illustrates the importance of proportion in classical architecture and the effects of violating such in width and height. See also section 24.1 on the golden ratio, 5, as a basis for architectural proportion in aesthetics. We would predict that the meaning of a set of observers will be higher in value when presented with the proportions of the original, figure 24.3, top, than those of the modified Parthenon, bottom. In the middle image we changed the number of columns from 492 Alexander J. Houston and Joseph P. Houston, figure 24.3 the Parthenon on the Athenian Acropolis, Greece. Top view represents the original, in the middle a column has been added, bottom view shows the result of vertical stretching. Aesthetic evaluation of art 493 8 to the uneven 9, which also influences the overall proportions of the building and eliminates the central space, which is an important Q in ancient Greek architecture. In architecture the proportions are closely related to structural variables such as the loads or forces applied to a structure or its components. These variables, which influence the necessary thickness of walls, columns, and floors, depend on building materials, regional. Figure 24.4 the pavilion by Mies van der Rohe built for the 1929 International Exposition in Barcelona. Top, original, bottom, violated. Photo by Ashley Pomeroy, Creative Commons, Attribution Non-Commercial License. 494 Alexander J. Houston and Joseph P. Houston Historical and intentional variables. Compare the proportions of the Parthenon with those of Mies van der Rohe's pavilion in figure 24.4. 24.15 Classical Modern The Bauhaus, founded by Walter Gropius in Weimar, Germany, 1919-1933, propagated the avant-garde of classical modernism in all of the free and applied arts. One of its guiding principles, Q, was the creation of a total work of art, a Gesamtkunstwerk in which all of the arts, including architecture, would eventually be brought together. Modular elements came to be employed in industrial structures and for creating affordable housing, major QS being industrial prefabrication, simple, cost-efficient manufacturing. In his Ver on Architecture, L.E. Corbusier proclaimed the principles of the new architecture to be based on functionality, with an aesthetic based on pure form, L.E. Corbusier 1927. His buildings, starting with Villa Savoye in 1931, exemplify his 5 principles, QS, of architecture. For example, Q1, the main building is often separated from the ground, supported by concrete stilts, allowing Q2, a free facade with non-supporting walls, and Q3, an open floor space. In the upper floors he employed large windows providing a wide open view, Q4. Roof gardens compensated for the greenery that was displaced by the building, Q5. L.E. Corbusier also followed the use of the golden ratio Q blended with human proportions in his buildings. An example of the new architecture is Mies van der Rohe Pavilion in Barcelona. Figure 24.4 the qualia in this work are not only visual, but especially of a conceptual nature. Free-flowing, open spaces were made possible by the removal of load-carrying exterior and interior walls and the use of slim, steel columns. The bottom of figure 24.4 shows the effect of replacing conventional outer walls and roofs to this building. 24.16 Minimalism has been practiced in the past inter alia in Japanese architecture, following ideas of Zen philosophy or the Japanese Ma, negative space. Modern minimalism evolved from the Bauhaus school which adopted Zen ideas of a radical stripping down ridding of ballast and excess information not germane to the main naked structure, message, and composition. As stated earlier, the common denominator of minimalism in the fine arts, literature, and architecture is to focus on the essence of a work, its abstract quality by the elimination of superfluous concepts and items. The emphasis in architecture was on QS of simplicity, basic geometric forms, cold and hard lighting, open living spaces, minimal use of materials, objects, and decoration, with the intention to reduce to the point where no further reduction could add to the concept. Note the aphorisms less is more, Mies van der Rohe, or less but better, Dieter Rams, by which the simplest and fewest elements are to be applied to produce a maximum effect. A great deal of attention came to be focused on clean spaces, natural light, and air in interaction with the inhabitant to achieve abstract qualities, QS, related to essential harmony, order, and simplicity, independent of tradition and historical burdens. Contrasting Wang Shu's minimal ceramic house with Frank Gehry's art museum in figure 24.5 highlights the obvious important aesthetic evaluation of art 495 QS in minimal architecture. Gehry's building is highly compositional, like a cubist painting, with QS of balance and the questioning of balance in form, light, shadow, and statics. It exemplifies modernist tendencies to QS of individualism, freedom of expression, and technological experimentation. Its parts could be arranged differently without sacrifice. Its design process is formal from outside to inside in contrast to Shu's design, which is causal and conceptual. The former design might invoke more central emotional QS in the viewer than Shu's with its emphasis, on the one hand, on conceptual intellectual mathematical QS and, on the other hand, on QS related to serenity, purity, the spiritual, the sublime, the poetic. Which brings us back to equation 24.4 and the prediction that the smaller the number of QS in the work, the more vulnerable will be the residual overall evaluation of the work to elimination or violation of any individual quality, and we can speculate as to which of these two works could more likely withstand an extraction or defacement of AQ. As emphasized earlier, such considerations and goals hold also for expressions of minimal art in painting, music, film, literature, and theater, where minimalism can be contrasted with past art forms often cluttered with decoration, symbols, of religion and power, etc., information, and facade. It isn't necessary for a work to have a lot of things to look at, to compare, to analyze one by one, to contemplate. The thing as a whole, its quality as a whole, is what is interesting. The main things are alone and are more intense, clear, and powerful. Judd 1965. Figure 24.5 left. Detail of Weismont Art Museum, Minnesota, USA. Architect, Frank Gehry. Photo by William J. Fox, ed. Right. Detail of Ceramic House, Jinhua, China. Architect, Wang Shu. 2012 Pritzker Architecture Prize. Photo by L.B. Hongshou. Courtesy of Wang Shu and Amateur Architecture Studio, Hangzhou, the People's Republic of China. 496 Alexander J. Houston and Joseph P. Houston. We can now refer back to equation 24.4, which predicts an inverse relationship between the impacts of QS in relation to their total number in the evaluation of a work, and ask whether this formulation does not provide a mathematically based explanation for the appeal of minimalism in art and architecture independent of the prevalent ideological/psychological rationales presented above. It follows that the equation would also allow comparisons between different art forms, such as schools of art, based on relative number of inherent qualia. Such congruence between predictions from this model with the reality of human evaluation argues, both, for the heuristic value of such modeling and for the utility of the concept of qualia in accounting for art evaluation. 24.17 How does the brain process qualia? As part of a collection of essays on aesthetics and the brain, this chapter should attempt to relate our approach to aesthetic evaluation to the prospect of eventually being able to understand the neurophysiological mechanisms that must underlie the processes of perception, recognition, and evaluation of qualia as espoused in our model. How can the nervous system cope with such complex processes, and how can we hope to discover the physiological basis for these processes? Each cue extracted from an image constitutes a separate complex representation in the brain at the moment of its recognition. If our viewing and evaluation of a complex image depends on the interplay between individual attributes or QS of an image, our nervous system must possess the mechanisms necessary to attend to, encode, recognize, store, and respond to such representations. Some of the required mechanisms involved include attention to the image, its registration and recognition, plus the processing of associative, emotional, reflective, and evaluative responses to the image. A vast research effort is engaged in delineating the anatomical, physiological, molecular, and genetic mechanisms involved in each of these categories of central nervous system information processing, which, in total, encompass the totality of neuroscience research, which subsumes many highly specialized disciplines. It can be expected that as these individual mechanisms become known, it will be possible to extrapolate to what happens in the brain during confrontation with in response to an image. In section 24.4 we presented a rough classification of QS based on 1. Simple basic stimulus properties, 2. Emotional QS, 3. Formal compositional QS, 4. QS with associated value of items or ideas, 5. QS, related to interaction between concurrent QS, and 6. Higher order QS. For our purposes it may be useful to attempt to relate these categories of QS to known major separable central neurophysiological subsystems involved in information processing. Some progress in understanding processes involved in our first three categories can be attributed to imaging experiments. The main contribution so far has been in analyzing aesthetic preference, that is, in discerning between like versus less like presentations on the basis of activation of corresponding structures in the brain, summarized in Cell-Conda et al. 2011. For example, neural activity can be registered in various brain areas while observers rate aspects of the presentation, such as beauty or symmetry, on some scale, and such studies have identified structures activated during evaluation of preferred images, such as the orbitofrontal cortex, Kawabaha and ZT aesthetic evaluation of ART 497-2004, left dorsolateral prefrontal cortex, Cell-Conda et al. 2004, left anterior cingulate gyrus and bilateral occipital gyri, Vartanian and Goel 2004, and frontomedian and anterior cingulate cortex, Jacobson et al. 2006. Given the realm of QS that can comprise the evaluation of images, reducing aesthetics to the experience beauty is, of course, a gross oversimplification of what will be required to account for the experience is derived from, for example, visual images or works of art. Beauty represents an overall evaluated response to an image and probably subsumes emotional properties related to bliss, joy, and reward, but the concept masks the constituent elements, QS, and processes that lead to such a response, and which must be the objects of an ultimate neuronal accounting for aesthetics. Several attempts have been made to delineate the sequence of brain areas activated during the presentation of an image with some success in identifying different areas engaged within milliseconds of exposure in correlation with processes of registration of, attention to it, aesthetic evaluation of, emotional response to, and engagement with the presentation, Chaturti 2004, Jacobson and Hopel 2003. Other brain imaging studies have focused on neural systems involved in recognition processes, the role of the brain's reward system, emotional responses, and the role of experience in viewing artworks. Summary in Cell-Conda et al. 2011. A meta-analysis of neuroimaging studies of positive valence aesthetic appraisal led to the hypothesis that a system for aesthetic processing initially evolved for appraising objects with survival value, e.g. food, and was later co-opted in humans for aesthetic experience to satisfy social needs. Brown et al. 2011. A number of studies have also dealt with the question of how object and action categories are represented in the brain. For example, functional magnetic resonance imaging, fMRI, was used to measure brain activity elicited by presentation of movies in order to investigate the cortical representation of 1,705 different object and action categories, Huff et al. 2013. The authors reasoned that, given the vast number of such categories humans can recognize, the limited size of the human brain would preclude the possibility that every single category is represented in a specific brain area. Accordingly, they found that object and action categories are represented in a semantic space consisting of at least 4 dimensions, and that this space is organized into smooth gradients covering most of the visual and non-visual cortex. The cortical organization of this visualized semantic space was invariant across different individuals. Thus, the brain represents object and action categories into a continuous space onto the cortical sheet so that adjoining points in the cortex represent semantically similar categories. However, other studies have shown that some categories of objects and actions are represented in specific cortical areas, such as for faces, Rajaimer et al. 2009, body parts, Phelan and Downing 2005, and outdoor scenes, Epstein and Ken Wisher 1998. A large effort is dedicated also to understanding how conscious perception evolves following presentation of a stimulus, Van Rooyen and Cook 2003, and the mapping of brain regions responsible for the encoding and retrieval of semantic and perceptual associations, Prince et al. 2005. Although some progress has been made in identifying brain systems involved in viewing and evaluating images, a major challenge for the area of neuroaesthetics research relates to the competition between different qualia that comprise the perception and evaluation 498 Alexander J. Houston and Joseph P. Houston of the image. We postulated earlier that qualia fade in and out as the viewer habituates to one or tires of it. Potentially, the kind of semantic organization of categories in the brain as demonstrated by Huth and colleagues, 2013, can provide a basis for investigating how the brain handles such processes, the rapid activation and alteration of representations of different classes of qualia. However, the brain's response to present representation of a display involves many separate neural systems with a continuous interaction between the perceptual, mnemonic, associative, attention, and emotional systems. An ultimate understanding of the brain's role in perceiving and responding to a complex display with multiple cues will have to invoke all of the systems involved in conscious and unconscious perception, information processing, emotional response, and internal mentation. 25.1 Introduction. How is it that some works of music, the most temporal of all art forms, can elicit an experience of timelessness? In this chapter I explore three pieces known to have such an effect: the haunting fifth movement of Olivier Messiaen's Quartet for the End of Time, Morten Lauridsen's quietly ecstatic choral masterwork O Not a Lux, and I'm Daffy Over You, a tune finely crafted to frustrate and annoy the audience, written by Chico Marx and Sol Bielinski. The effects of these works on listeners can be explained only if we acknowledge that our experience of subjective time is more complex than usually thought. In particular, it may include not only sensation but also a purposive stance, particularly involving the anticipation that is crucial to music. Fortunately, one of the traditions in musical aesthetics can help us begin to articulate this experience, and it is complemented by recent neurophysiological insights. Such an approach may also clarify the remarkably enduring gifts of Clive Wearing as described by Oliver Sacks. 25.2 Preliminary considerations in traditional aesthetics. Formalist theories hold that the pleasure we get from music is a cognitive pleasure. We enjoy recognizing the structure of music. There is some neurophysiological support for something similar to this. Chenier and Winkelmann, 2009, offer a hypothesis of aesthetic pleasure as arising from processing fluency, that is, sensory perception and its related information processing occurring with increasing ease. This fluency increases with repetition, perhaps by lowering the threshold for stimulation of the relevant neural pathways, perhaps by successively pruning away responses to auditory elements regarded as irrelevant. We are also more fluent at processing groupings that are structurally related rather than arbitrarily clustered, e.g. in language we more easily recognize grammatical strings of letters rather than arbitrary ones. Symmetrical or otherwise simple sensory objects which thus have less information lend themselves to processing as well, as do prototypes or averages of categories. The first measures of a song that is recognizably a ballad or a patter song or some other genre render it more predictable in a pleasant way. Competing with the formalist theories, there are expressionist theories of musical aesthetics which explain aesthetic pleasure as pleasure in somehow sharing the emotions that tempos of eternity 501 the composer expresses through music. This approach too has some neurophysiological evidence. In one recent study, listeners' reports of subjective pleasure in listening to their favorite music and to neutrally valued music was strongly correlated to various objective measures of autonomic nervous system arousal, such as electrodermal activity, heart rate, respiratory rate, temperature, and blood volume pulse amplitude, and thus, presumably, to emotional arousal. Salenpo et al. 2009. Interestingly, intense pleasure could be taken in either happy or sad music. The pleasure's intensity was related to how emotionally arousing the music was, regardless of which emotion was involved. Another study found that openness to sharing the emotion represented also increased the emotional response to music. Opera listeners in a cognitive state of empathy with the character singing responded with greater reported feelings of emotion and greater physiological parameters of emotional arousal. Mew and Baltz 2012. These two kinds of theories now appear to be more complementary than competing. But even taken together, they may not be sufficient as a way of explaining this phenomenon. A third major tradition in musical aesthetics, influential within the classical music world, has received surprisingly short shrift outside that community. This tradition emphasizes the driving force over time that we experience in music, the anticipations, conflicts, and resolutions we live vicariously through music. The 19th century philosopher Arthur Schopenhauer built his metaphysics to accommodate music as one direct expression of a universal will, just as he regarded life itself as another direct expression of this will. Schopenhauer 1966. Not surprisingly, many prominent musicians, including Wagner, Brahms, Bach, Mahler, Rimsky-Korsakov, Schoenberg, and Prokofiev, have admired Schopenhauer's philosophy and the importance it places on music, whether they accepted it as metaphysically true or merely as an astute phenomenological description. Point one: American pragmatist philosophers avoided such metaphysical speculation, but their interests in psychology led to similar themes and influenced musicologists such as Leonard Meyer and David Huron to develop analyses of music based on listeners' anticipation of and desire for impending notes and harmonies. These approaches could perhaps be loosely categorized together as emphasizing the purposiveness or future-directedness of music, whether we think of it in terms of listeners' anticipation, or the teleology implicit in the work's cohesion over time, or the music as guiding our attention, our volition, or even our movement. These approaches would incorporate both the intellectual musical structure of formalist theories and the emotions of expressionist theories as important aspects of any work of music, as contributing to its overall momentum. These last aesthetic theories are particularly valuable for current neurophysiological exploration since they allow us, more than the other theories, to articulate the temporal aspects of music and the structure of experienced time, and time is a dimension increasingly vital to neurophysiology. In this chapter, I shall briefly summarize how these approaches to music could be combined with recent neurophysiological data to clarify how our rhythm, anticipation, and motility interact with music. These approaches solve one apparent paradox about how 502 Barbara G. Goodrich certain musical works elicit a sense of timelessness or eternity in the listener. In exploring two such works, and one song designed to elicit the opposite sense, frustration, in the listener, I shall suggest a hypothesis about the structure of subjective time as involving an interaction between perceptual processes and volitional or movement initiation processes. 25.3 Rhythm, anticipation, and motility/volition. Listen to Tchaikovsky's 1812 Overture. At some points, your heart rate will probably speed up considerably. The Adagietto from Mahler's Fifth Symphony, on the contrary, seems to slow a listener's perception down to the precision of time-lapse photography. Rimsky-Korsakov's Flight of the Bumblebee may make you feel as if you have had too much coffee, but need even more, and like it. On the other hand, Pachelbel's Canon in D major, if aimed at telephone customers trapped on hold, can make 30 seconds feel like eternal damnation as imagined by James Joycean Priest. For good or ill, music can alter our sense of time's passing, its duration, its rate, its continuity, its quality. 25.3.1 Rhythm. Recent advances in physiology present plausible lines of inquiry about how this might occur. Thought, 2005, suggests that when we perceive musical rhythm, we aren't passively counting durations of external timekeepers, or comparing external durations to some absolute internal counter, as some traditional theories of time perception hold. Instead, we are interpreting the rhythm through our own complex and often changing biological rhythms, the ongoing to and fro oscillations of countless ion gradients in neurons and muscle cells, of respiratory cycles, and so on. Point two: Listening to music is not a disembodied God's point of view affair. When we listen to music, we aren't counting the beat, we are interacting with it, even living it. For example, pulse rates close to the physiological heart rate, between 60 and 150 beats per minute, BPM, are easily interpreted as musical tempos. Pulses faster than 300 BPM tend to be perceived as subdivisions of a tempo. Pulses slower than 30 BPM tend to be heard as multiples of a tempo. Thought 2005, P9. Oscille rondos and retardandos are more complicated. With them, we must recognize the pulses as a continuation of the rhythm despite their change in duration, and we must simultaneously recognize that they are slowing down or speeding up, which requires some implicit background of a steady beat, possibly from neural oscillations, contrasting with the rubato. It may help to remind ourselves of the Gestalt structure of perception. In normal perception there is no single datum, no single isolated pixel or indivisible moment of sound. Instead, we perceive patterns, comparisons, and contrasts. Point 3: We focus our attention on some sensory input as a foreground against the rest of our perceptual field, which remains in the background, preconscious but nonetheless framing the foreground, influencing how we perceive it. The rhythm of music is usually part of that background, framing and structuring the melody, which is typically the foreground on which we are concentrating. Point 4: The tempos of eternity 503. As 20th century philosopher and psychologist Maurice Merleau-Ponty points out, our bodies themselves provide a second perceptual background, composed of our heartbeats, our respiration, our habits of movement and perspective, language, and now we can add neuronal oscillations and language. Point 5: These frames of any perception, implicitly comparing and contrasting with it, are a large part of what gives a sensation its timing, its role in the perceptual field, and its meaning. In the case of the Tchaikovsky, the tempo of some sections may even directly entrain the heart rates of listeners, slowing and then speeding them up to a rate associated with excitement. The dazzling speed of the piece by Rimsky-Korsakov makes it a challenge even to follow, but the insistent, amusing melody seizes our attention again and again, in a playfully disorienting way similar to the effect of watching such an insect without the risk of being stung. We want to follow that sound, even if it evades us from time to time. 5.3.2 Anticipation. What of the melody in harmony? Many musicologists regard anticipation of impending notes and harmonies as central to music. For two theorists, Meyer, 1961, and Huron, 2006, the core of music is its setting up our expectations of the next notes and chords, and either fulfilling or thwarting those expectations. The biological mechanisms underlying these effects are now beginning to be clarified. For example, our response to a surprise, even merely an unexpected musical harmony or rhythm, involves a single afferent pathway which then diverges at the thalamus into two tracks. The faster track goes directly to the amygdala, causing reactions ranging from fear triggering the autonomic release of epinephrine to the mild disorientation of perceptual field that can accompany a failed prediction. The slower track takes a detour through the sensory cortex before arriving at the amygdala, and incorporates conscious appraisals of the situation. These more considered responses can modify the fast track's automatic reactions, for example, changing a negative valence to a positive one. However, these two overlapping tracks are also interacting, in that a greater surprise can increase the pleasure of a pleasant outcome by its contrast. Huron's example is of someone startled by a surprise birthday party, with momentary fear changing quickly to pleasure. Musical tension, the delay of an anticipated resolution, is in many ways the opposite of surprise. In Western music, much of what drives a melody is our preference for ending on the tonic note, the home bass note of the key. We don't feel closure or satisfaction until this is reached. Certain chords, e.g. the dominant seventh of any particular key, make us expect an immediate return to the tonic, an immediate resolution. Other chords and phrases suspend the resolution for beats, bars, even minutes, and manipulate our expectations in subtle and sophisticated ways. Just as when listening to someone speak, we constantly reinterpret a spoken syllable according to the most likely word it may be introducing, we also reinterpret individual notes and chords in the light of possible phrases and resolutions to come. Delaying the expected resolution draws our attention and prompts us to imagine that resolution. To want it more. 6 The Adagietto from Mahler's Fifth Symphony is built from lengthy suspensions in which our anticipations of harmonic resolution are 504. Barbara G. Goodrich, frustrated by unexpected dissonances and eventually rewarded only when we are minutely engaged with the melody. Perhaps this is why every second seems so full while we are listening to it. Why do we feel this pull towards musical resolution? That is still unknown, but researchers have recently discovered preferences for certain pitches and intervals, and have correlated consonant intervals with greater neural synchronization, and dissonant intervals with less neural synchronization. Feidelman and Krishnan 2009, Watts and Stone 2008. There is a measurable neural substrate for the preference for harmonious resolutions. And insofar as musical conflicts, surprises, tensions, and resolutions mirror our nervous and endocrine system's tendency towards healthy homeostasis, towards pleasure and happiness, they may be experienced as mirroring our own volition, allowing us a vicarious sense of fulfillment. 725.3.3 Motility/volition for humans and some bird species, at least. Music can also recruit our volition in the sense of encouraging us to initiate movement. Our motor areas, including the cerebellum and basal ganglia, are activated not only when we are already moving in response to music, but even when we are merely perceiving it. Graham 2009. Because of these close connections of auditory pathways and motor pathways, we can synchronize our movements to anticipated beats by a feed-forward mechanism, anticipation, again, in training us into those famously contagious motions of hand clapping, nodding, marching, or dancing to music. Thought 2005, P45.8. After all, music works by the same rhythms that serve as a scaffold for our own movement and sequential skills. Conway et al. 2009. We spontaneously want to move to it, to synchronize with it. Because of this predisposition, Thought 2005, and others, e.g. Sachs 2007, have been able to use music with striking success in helping Parkinson's disease patients recover initiative in movement. The effect of music on our tendency to move may reflect an even deeper influence by music on us than usually thought. Two leading neurophysiologists, Kozaki, 2006, and Lenas, 2001, have hypothesized that consciousness itself evolved as an aid to motility. If this is correct, it would account for how crucial future-oriented purposiveness or volition is to our experience, as well as this drives elusiveness to reflective self-awareness. It would be too primordial to be easily represented or verbalized. Goodrich 2010. Because of the primacy Kozaki attributes to motility, he suggests that we reconsider how we think of sentient animals in their environments. Rather than a circuit of perception triggering a behavioral reaction whose results are then perceived and so on, it may be more accurate to think of the ongoing circuit as beginning with subjects acting in their environment and then perceiving the effects of their action, which prompt more action from them. In any case, there is a finely tuned ongoing circuit of action and perception in any sentient animal's interaction with its environment, from a bird's balancing its weight on a branch in a strong breeze to two humans waltzing with each other in time to music. Overall, then, humans are influenced profoundly by music in many ways. Some music is able somehow to cause direct emotional arousal in many people, complete with chills and tempos of eternity. 505 dopamine release at the listener's favorite moments. It can alter our biological rhythms, and our perception of time. But more than that, by engaging with and altering our expectations, many musical works are able somehow to recruit our volition itself, seducing our attention, and training even our movements. If it were not so widespread as to be taken for granted, this effect would appear to be magical. 5.3.4 Note on volition. Some researchers have avoided the notion of volition or will, terms used synonymously here, partly because its sources aren't terribly clear even to the individual willing, partly because it resists measurement, and partly because the term is used for a variety of meanings: agency, a sense of agency, initiating movement, drives, telos, forming long-term plans, directing attention, choosing among options, inhibiting possible actions, and so on. These are genuine problems. However, in some topics the notion is unavoidable, and it appears to be gradually undergoing rehabilitation as a needed and legitimate focus of research. One misguided reason for avoiding it is the problems that arise when we imagine that one's will must be fully conscious and free, and disembodied. 9 Many Westerners still believe, with Kant, that such a radically free will is required for ethical and legal responsibility. But almost invariably the existence of free/conscious will is undermined by empirical data and even by our own embodied experience. Further, Westerners tend to devalue semi-conscious, pre-conscious, emergent, and habituated actions and intentions as mere mechanical processes, overlooking the subtly but profoundly different Gestalt possibilities inherent in any complex sentient organism. Thus Libet, 2004, after finding data inconsistent with the notion of a fully conscious free will, bit the bullet and ingeniously salvaged what he thought he must to retain human responsibility, the conscious mind's ability to veto subconscious urges as free will. I suggest that we abandon this problematic notion of radically free will and instead explore human volition using the criterion of a sense of agency, that is, whether we experience volition as ours, as expressing ourselves, as opposed to us being constrained or undergoing simple reflexes. One's volition would include subconscious or preconscious forces such as predetermined instincts, parental instincts or mere instincts, but are also part of the deepest core of oneself, both socialized habits and self-made habits, the latter allowing a measure of freedom since one's future self is in part a creation of one's present self, and autobiographical learnings, as well as reflective decisions about long-term goals. With regard to physiology, perhaps the main determinant of our sense of agency, of whether our actions are due to our own volition, is the fluency with which we select actions, monitored as we select them by the inferior parietal cortex. Chambon et al. 2012, Haggard 2008. This seems roughly to indicate how congruent we feel about the action, and, significantly, that fluency is not limited to conscious and non-stimulus prompted actions. Yet after all, unconscious information processing can be flexible, adaptive, sophisticated. Watt et al. 2011. Admittedly, this sense of agency is not infallible since it can be manipulated. Chambon et al. 2012, and inevitably there are gray areas. Even these 506 Barbara G. Goodrich weaknesses, however, contribute to its fitting the ordinary use of the term volition and will surprisingly well point 10 incidentally. Commercial law is ahead of many philosophers with this notion. For example, in the law of economic terms what matters is not the absolute freedom of the contracting party, but rather the nature of the pressure to which they are subjected. Atlas Express v. Kafko, Importers and Distributors, LTD 1989 QB 833. In other words, the legal arbiters of human responsibility do not require the kind of absolute freedom of will for which some psychologists and philosophers are still searching. 25.4 Music and the temporality of consciousness. One of the important insights from these physiological accounts is that there is no present moment isolated from past and future. There is not even an instantaneous present moment for the listening brain, as Krauss, 2011, demonstrates. Even a single click lasting 0.1 millisecond is processed in the auditory brainstem over about 7 milliseconds. The experienced present is saturated with memory and anticipation as well. How we perceive a current chord depends on previous chords and phrases, anticipated ones, genre, etc. Analogous to how we perceive a single syllable. Point 11. We are not timeless beings observing a world unfolding before us. We are unfolding through time ourselves. There is a major puzzle, though. Certain works of music famously elicit a paradoxical sense of eternity or timelessness in many listeners. How can this occur? Let us examine two of those works. I shall present a hypothesis as to how they could have such a baffling effect. If it is correct, it would have important implications for time perception as a whole. I recommend that readers listen to recordings of each piece before reading the descriptions following. 25.4.1 Messiaen's Quatuor pour l'off in deux temps, Escaping Time into Eternity. Olivier Messiaen's moving, dissonant 1941 Quartet for the End of Time is one of the key works of 20th century music. The quartet was written for an odd combination of instruments, violin, clarinet, cello, and piano because those were the instruments to which Messiaen had access in a concentration camp during the Second World War. It is an assertion of a pacifist Catholic's faith from the depths of war, although it has transcended its specific original religious context to establish new norms in Western classical music in general. Nonetheless, Messiaen conceived of mundane time as emerging from a timeless eternity, and sought to change his listeners' focus from particular events in time, such as the war, to the larger timelessness of mysticism. This is especially true of the fifth movement, the only one with eternity in its title, Louange à l'Éternité de Jesus. This movement is a duet. Soft piano chords play a background pulse at a tempo marking of infinitely slow, ecstatic, and the cello draws out a poignant, slow, sustained melody line. The effect on the listener of escaping time is intense enough that one eloquent philosopher of aesthetics does not attempt to explain it naturalistically, but regards it as gesturing towards the possibility of something timeless beyond nature. Colquima 2009. Tempos of Eternity. 507 music scholars have analyzed the quartet for the End of Time for its extraordinary use of unusual rhythms, tempos, and tonalities to disrupt the normal sense of time continuity. Point 12. The rhythms in the quartet are frequently disconnected from the meter, and in the fifth movement, there is no explicit meter. The beats per measure vary, as do the length of individual beats. The piano's groups of 4/16 notes expand to 5, shrink to 3, and so on. Nonetheless, the piano part consists solely of 16th notes, played at an extremely slow x equals 44, limiting any sense of obvious rhythmic phrases but keeping a slow pulse. Below is a representative line. See figure 25.1. The cello part is one long melodic arc, incorporating isorhythmic phrases, accents both on and off beats, slow dynamic changes, and a slow return to the tonic that gives a sense of peaceful resolution but not finality. The different analyses of Messiaen's techniques explain the sense of temporal disorientation we experience at different points in the quartet, the mismatch between expected rhythms and actual ones, the loss of a temporal anchor, but to my knowledge there is no account for the fifth movement's paradoxical sense of escaping time. Merleau-Ponty's description of the perceptual gestalt, in particular with the second background of one's body, may be able to do so. Normally, a background beat serves to mark time, and against it the melody stands out, but the very slow background beat of the soft piano chords, played as slow as 44 beats per minute, is close to the lower limits of the human ability to recognize a beat as a beat. 2005, P9, and it is slower than most normal human heart rates. If a listener's heart rate could be entrained by such a slow tempo, then the beat, synchronized to the body's own second background pulses, might conceivably fade into that second background enough that it no longer functions to interact with the cello melody in the conventional way. As thought, 2005, writes, notes occurring with a piece's underlying pulses are regarded as low-level information and tend to be overlooked. If the music's almost subliminal pulses have converged with the listener's own pulse, they could be difficult to notice, despite continuing to function as pulse markers. Instead, one's conscious auditory field can be filled entirely by what would normally be only the perceptual foreground, that is, the slow, sustained, deeply emotional cello line. We come almost to identify with the cello's sustained note. Though it moves and changes, our attention is carried along with it without the usual rhythmic point of reference. Figure 25.1 excerpt from Messiaen's Louange à l'Éternité de Jesus. Copyright Durand Editions Paris. All rights reserved. Reproduced by kind permission of Hal Leonard MGB, Italy. 508 Barbara G. Goodrich. Here is my suggestion. Experienced time is not caused by any single pacemaker or any single oscillation. It is caused by the interaction between at least two different processes, causing a sense of friction, as it were, between them. It is premature to speculate about what the neural mechanisms might be, though one suspects dopamine may be involved at some point. Phenomenologically, though, as Merleau-Ponty, 1962, describes, we tend to sense a kind of friction or intersection between a more receptive aspect of ourselves, formed by perceptions and memories, and a more active, future-oriented aspect of ourselves, formed by anticipations, intended goals, initiative, and motility. Normally in each moment of consciousness there simultaneously exist memories and habits from the past, present perceptions, and aspects of future-oriented volition, be they emotions, plans, anticipations, decisions, intentions. Attention. Point 13. However, these seem to be organized into a kind of gestalt. The foreground of this temporal gestalt is the future-directed aspect of ourselves against the background of memories and perceptions. We are, Merleau-Ponty, 1962, p. 428, writes, simultaneously passive and active, recipient and agent. Our temporality is the basis both of our activity or individuality, and our passivity or generality, that inner weakness which prevents us from ever achieving the density of an absolute individual. This description accommodates our subjective time speeding up or slowing down. Our usual sense of time might result from internal interactions, the friction, so to speak, between some of these different processes. When our sense of time is altered, this might be caused by a change in how those two kinds of process are interacting, disrupting each other, generating greater or less internal friction. When we are waiting in line, there is more friction, so to speak, and time seems to go more slowly. When we are sipping a good whiskey with friends, there is less metaphorical friction and time seems to fly by. Point 14. More rarely, if one of these two aspects, roughly speaking, we could perhaps refer to them as perception and volition, temporarily overwhelms the other, the whole structure of the interaction can be changed or even temporarily collapse. This is a useful model for thinking of pathological distortions of experienced time, for example, in psychological shock, in schizophrenia, in Parkinson's disease, and in clinical depression, and it is telling that in each of these pathological cases there are also disturbances in initiative. In the case of the Messiaen, the friction is removed by the background rhythm fading into our own biological rhythms. An actual solo for cello might invite the listener's imagination to fill in the pulses of the piece, so that the listener might have a stronger than usual sense of its rhythms, and its progression through time. Point 15. But a slow, barely perceptible background pulse such as in this work, by discreetly blending in with the cardiac oscillations, seems to remove entirely the experienced friction between intention and perception, temporarily dismantling the structure of subjective time itself. By this account, we've indicated how the effect of escaping normal time into a seemingly supernatural eternity could be caused by natural means precisely because it is based in the rhythms of the changing organism, the depth into the, well, almost heart-stoppingly beautiful cello line. Tempos of Eternity. 509 to 5.4.2 Lords and Sonata Lux, Glimpses Beyond Time. Morten Lordsson is a contemporary US composer, not yet fully celebrated. O Nautilus is in a cappella motet, the most meditative of the songs from his 1997 Lux Eterna. Like his more well-known 1994 O Magnum Mysterium, it deftly combines understated features to stunning effect, the long elastic phrases and subtle hesitations of Gregorian chant, simple Renaissance harmonies and counterpoint, and modern touches. Upon their debuts, these works were instantly acknowledged as making choral history, and have since broken out of ecclesiastical circles to achieve critical renown and growing popularity in the larger secular classical music world. Lordsson's style might be compared very roughly to Arvo Pärt's in its surface simplicity and reverence, but I find it far more nuanced and unself-conscious, despite, or perhaps because of, its roots in the oldest surviving traditions of Western music. The quiet mastery of Lordsson's compositional techniques avoids the sentimentality risked by any work aiming unabashedly at pure beauty. This section incorporates insights into this piece's remarkable effects from distinguished choral director Alison Olsen. Point 16. Some of the descriptions are inevitably technical, but non-musicians will be able to understand the main points. The motet is set for a full a cappella choir of sopranos, altos, tenors, and basses, and each of these four voices splits into two parts at some point or other, frequently having 5 or 6 notes sung simultaneously. The gentle, weightless melody line of isochronous eighth notes in 4/4 meter is repeated by different voices at different times, often overlapping each other in a wave-like pattern. In his advice to musicians, Lordsson emphasizes that this motet is based on chant. He insists that the singers should not be thinking vertically, in chords, but linearly, with long melodies and a flowing give and take, a push forward and fall back to make the moment at the end of the phrase last a bit longer. Lordsson et al. 2008. This hesitation is part of traditional Gregorian style. It also, significantly, matches the slow human respiratory rate. When the overlapping voices end a phrase simultaneously, this occurs in an isolated 3/4 measure, drawing back very briefly and holding the final note to create a moment of something like suspended animation. The effect is almost of another 4/4 measure, but not quite, and this difference is slightly disorienting even as it aligns itself with our breath more precisely and familiarly than a straight 4/4 beat. The tonality at first seems traditional and simple, but there are ambiguities and sophisticated changes within it. The overall form of the song is a modified AABA form, 12 measures in the key of D major, then a middle section of 10 measures of ambiguous tonality functioning mainly as A major, then a 3-measure transition back to a restatement of the opening passage again in D major, finally resolving and ending with a 7-measure coda. Olsen points out that Lordsson only twice uses the tonic D chord in the standard root position. For non-musicians, think of the usual bottommost note, the home bass note at measure 23 when returning to the key of D major, and at the piece's final resolution and coda beginning at measure 35, in other words, at the only 2 times when the melody is hinting at a sense of completion. Elsewhere, the D chords nearly always have the third, 510 Barbara G. Goodrich F sharp, on the bottom, leaving the tonic root absent. This is a device Lordsson borrows from Renaissance music, and it gives a floating, unanchored feeling. This is not the feeling of a question that needs to be answered, or a puzzle that must be resolved, but it is the sense of not quite completeness, of something waiting for finality. Lordsson's signature chord, for this piece and for others, includes this third, here, F sharp, on the bottom, then the tonic an octave higher than expected, here A D, then the keys 9th, E, and the dominant 5th, A, at the top. Including the 9th in a tonic chord is a 20th century innovation, found frequently in the playful, merely disruptive final chords of jazz songs. However, when hidden in the middle voices as it is in this particular chord, this added note is more gentle. It enriches the sound while also hinting at an ambiguity of tonal centers. The unexpected E note may be the unconventional 9th to our tonic D, but it is also the important dominant 5th overtone of DS on dominant 5th overtone, A, which is emphasized in this chord at the top. In this way, even when stopping on the resting tone, D, the listener still hears hints of another tonality, A, see figure 25.2. It is almost analogous to what are known as ambiguous gestalten, visual images such as a duck-rabbit cube that can be interpreted in either of 2 ways. What we would need to complete the transition from the key of D to the key of A is to change the G natural to G number. The occasional accidental of G number appears briefly several times in the bass before it finally becomes the norm in the soprano line to mark the start of the middle section at measure 13. After the return to the key of D at measure 23, it recurs several more times in the bass. Lordsson often uses the added G number to build an E major chord which, when juxtaposed with the D major chord, gives hints of a whole tone scale, adding to the feeling of indeterminacy as in measures 9 and 10. Whole tone scales are symmetrical throughout, so they lack any hierarchy. Because of that, they lack a clear home bass note, lending a feeling of dreamy indeterminacy to the sound. Olsen speculates that another harmonic factor fostering ambiguity is Lordsson's almost complete avoidance of the explicit A major chord in the D major sections of the piece. A major is the dominant, B, chord for the key of D major. Lordsson builds many of the chords in these sections with notes from the tonic chord and from the 4, subdominant, chord, G major, G natural, here. These 2 chords share the note D, yet have 2 other different notes each. The tonic sound is reinforced, but with extra notes blurring the sense of harmonic progression usually found in Western music. Lordsson also places more emphasis than usual on the alto voice, so that the highest soprano voice is no longer the obvious melody but functions as an overtone to the alto line. As a result, the often overlooked middle voices assume a greater importance, and the simultaneous melodies of the polyphony prevent any single voice from being highlighted over the others for more than a measure or 2. There is no single lead voice and there are no backup singers, all the voices are integral. Throughout the piece, much of the momentum occurs half hidden in the middle voices. For example, measure 31 has a series of chords incorporating second intervals in them, leading to another iteration of the signature chord with an extra A in the bass at measure 32. The listener is engaged in the experience of movement, but it is not in reaction to obvious change. Instead, the soft focused tonalities merely shift among themselves, in the background, so to speak, rather than in any foreground melody. These many tonal ambiguities do not demand resolution, however. The consonant harmonies, the repetition in overlapping waves, the sense of floating throughout, allow us to relax into them. Even when there are hints of a whole tone scale, the overall order of the simple, intuitive Renaissance harmonies introduces us to them with enough familiarity that we feel not presented with a problem to be solved, but rather gently invited to peek into the new possibilities. They function almost as a shimmering of possible gestalt shifts, with, for example, the key of A major partly hidden behind that of D major, and each of the 2 keys assigning different meaning to each note. The result is subtle, almost subliminal, but profound. Psychologists speak of ambiguous visual gestalten as unstable, but the experience here is too orderly and peaceful to be described in that way. Instead, the hinted D major key is presented almost as an additional new dimension that one could enter, depending on the next few notes. And it is this chord that is frequently formed when all 4 voices end a phrase together, and we feel a glimpse into possibilities usually beyond our perception. Lordsson has masterfully balanced numerous different tendencies in the listener so that no single instance of melody springs univocally into the foreground. The melody is effortlessly recognizable, but it also functions as overtones to other phrases, and as echoes of other phrases. It is part of the larger flow, and that whole flow is indicating possibilities of tones beyond itself. We find ourselves releasing our usual constraining focus of attention, our agenda-driven volition, our control over our attention in order to absorb the nuances that we cannot consciously trace out. As we do, the everyday gestalt structure of our perception is subtly but radically altered. The musical foreground and background blend together, and as they do, the distinction between listener and music as well seems to dissipate. The perceptual field temporarily suffuses what Merleau-Ponty called the second background of one's body. Then, when the flow of music holds back, we are brought with it into a momentary stillness of rare tranquility and openness to our surroundings, with an attitude of wonder at least temporarily. This experience is precisely not escaping the changing natural world into an eternity beyond it. It is engaging fully with the world, within time. To 5.4.3 Chico Marx's theme. From the sublime to the ridiculous, this third musical example is Chico Marx in Soul Violinski's I'm Daffy Over You, as played by Chico in Animal Crackers. This is a deliberately, brilliantly execrable little ditty designed 512 Barbara G. Goodrich to elicit something like road rage in the helpless listener, and worth purchasing the film to hear. At one point in Chico's performance, he is audibly counting the beats. Groucho, in the audience, impatiently tells Chico if he gets near a song, to play it. Chico explains that he can't think of the finish. Groucho, that's strange, I can't think of anything else. Chico, you know what I think I went past it. Groucho, well, when you come around again, jump off. We do not get a sense of eternity with this song, we are merely afraid that it may take forever. Chico achieves almost the maximum annoyance possible. He bangs out the repetitive melody slowly in high octaves, and with the tonic firmly, intractably in place in the left hand. Not only does he avoid playing with any kind of phrasing, he actually emphasizes the last note of the first phrase with an ad hoc tremolo, played with muscular gusto. The first brace note in the next phrase gets our hopes up for a reprieve from the monotony, but it is quickly revealed as the first of several measures of an odious little filler. When he reaches the end of those 4 bars, we are desperate for another change. And with the reappearance of the horrible octaves, we realize with a burst of laughter at Chico's slyness that we should have predicted exactly the return. Note that the song isn't just unpleasant to hear. It's frustrating, thwarting. It is an affront not merely to our perceptions, but also to our sense of agency, to our volition. It's the same sense as one's blood pressure rising in response to a traffic jam delaying an important appointment. And each additional obstacle, especially a predictable one which one can anticipate but not prevent, grinds time more and more slowly, as the status quo exerts more aggravating friction on one's plans. So it's not surprising that a musician with more schadenfreude than the amiable Chico can increase the effect of listeners' frustration by slowing down the tempo even more. 17 This is different from the much more common earworm phenomenon, in which a fragment of an annoying tune is repeated intrusively in one's oral imagination against one's will. 18 In the case of earworms, the culpable tune is typically just some recent and overplayed popular song. The granddaddy earworm, now thankfully obscure, is King and Harold's 1930 19. In some cases, the vividness and intractability of similar unwanted musical imaging can approach hallucination status. 20 Yet these cases are more mundane inner conflicts. The structure of volition or attention itself remains intact in each of its different foci. Terrible music must be dispelled, versus catchy tune must repeat. Chico's ditty can function as an earworm, but it also has the more sophisticated power of recruiting some aspect of our volition against it, dragging the flow of subjective time. 21 25.5 Clive Waring's enduring musical gifts. The importance of volition for the experience of time and for musical performance is seen in the case of British composer and conductor Clive Waring, a case made famous by Sachs, 2007, pages 201-31. In 1985, encephalitis destroyed about 20 years of Waring's personal memories, and, most devastatingly, almost all of his capacity for even short-term episodic memory. While his semantic memory of, for example, language and facts, was partly unaffected, up to his life in the 1960s, he lost the ability to remember where he was, whom tempos of eternity 513 he was with, and so on beyond just a few seconds. However, Waring's partly functioning semantic memory and sociability have enabled him to maintain some social connection, helping to ward off his agonizing disorientation in time. Even with a terribly constricted memory, he converses cheerfully. Waring's procedural memory for many activities has fortunately remained intact. He shaves, dresses, retrieves cups from the kitchen, makes coffee, dances. Astonishingly, his procedural memory for playing music is also intact. While he can't remember having played or learned any piece of shown his old sheet music, once someone else initiates his playing it, he can continue uninterrupted until the end, many minutes later, far longer than his episodic memory could track. He can conduct lengthy pieces. Even more astonishing, his formidable capacity for playful musical improvisation remains. The creativity in Waring's music is unexpected, since procedural memory is normally thought to be somewhat mechanical, a set sequence of movements, rendered automatic by concentration and repetition. Thus Sachs regards this intact creativity as puzzling. Each time Clive sings or plays the piano or conducts a choir, automatism comes to his aid. But what comes out in an artistic or creative performance, though it depends on automatisms, is anything but automatic. The actual performance reanimates him, engages him as a creative person, it becomes fresh and alive, and perhaps contains new improvisations or innovations. Once Clive starts playing, his momentum, as Deborah writes, will keep him, and keep the piece, going. Sachs 2007, p. 224, Deborah Waring describes an instance of this. The momentum of the music carried Clive from bar to bar. Within the structure of the piece, he was held, as if the staves were tramlines and there was only one way to go. He knew exactly where he was because in every phrase there is context implied, by rhythm, key, melody. It was marvelous to be free. When the music stopped, Clive fell through to the lost place. But for those moments he was playing he seemed normal. Sachs 2007, pages 224-5, how can automatic procedural memory enable this expansion beyond his usual limits, this return to his exceptional creativity? Sachs's answer is that a piece of music is an organic whole, and each present note strongly implies the past and future ones, more than our usual thoughts and anticipations do. Playing one chord of a piece will bring to mind, as it were, the rest of the piece, in a way that is not captured by the usual notion of memory. When we remember a melody, it plays in our mind, it becomes newly alive. There is not a process of recalling, imagining, assembling, recategorizing, recreating, as when one attempts to reconstruct or remember an event or a scene from the past. We recall one tone at a time and each tone entirely fills our consciousness, yet simultaneously it relates to the whole. It is similar when we walk or run or swim, we do so one step, one stroke at a time, yet each step or stroke is an integral part of the whole, the kinetic melody of running or swimming. Indeed, if we think of each note or step too consciously, we may lose the thread, the motor melody. It may be that Clive, incapable of remembering or anticipating events because of his amnesia, is able to sing and play and conduct music because remembering music is not, in the usual sense, remembering it all. Remembering music, listening to it, or playing it, is entirely in the present. Sachs 2007, pages 227-8, it is entirely in the present in the sense that we are fully reliving it, bringing the past into the present moment and letting it direct our attention towards the future. 514 Barbara G. Goodrich. If we apply Merleau-Ponty's description of consciousness in time, with its dual aspects of receptiveness and volition, Waring's continued musical gifts make even more sense. Playing memorized music is not merely executing a program contained within memory. It is instead goal-directed behavior, within the composer's given but not overly strict rules, in which there is a clear temporal gestalt. Within those rules, personal creativity and expression are permitted, even facilitated, similar to acting or dancing a dramatic role after one has memorized the character's script or choreography. Because a piece of music is more integrated than, say, an impromptu conversation or even monologue, the goal of continuing the gestalt exerts a stronger pull and coaxes more continuing action by more momentum. By the same token, beginning a piece might be more difficult, hence Waring's need for others to initiate his playing. Waring's case also may illuminate how highly integrated the volition perception circuit is. It is crucial to his circuit that it be ongoing, and in his case it is precisely the ongoing long-term, non-musical feedback from his environment that is interrupted. But as his memory gradually improves, and as his musical activities continue, Waring is reclaiming his life. 25.6 Conclusion. By drawing from Schopenhauer's and Huron's musical aesthetics as well as Merleau-Ponty's psychology and much recent neurophysiological data, we can begin to build an account of how the most temporal of art forms can, in certain cases, elicit a paradoxical experience of timelessness. This account relies upon the notions of anticipation and purposiveness or volition, which are involved in listening to music as well as in performing it. This account also suggests that our perception of time is derived not from a single counter or oscillation, but from the interaction of at least two kinds of rhythmic biological processes, perhaps one associated with motility or volition, and one associated with perception.